I'm going to show you how to find the number of significant figures in a number. These 4 rules will tell us how many significant figures there are in a number. I'm going to post numbers here on the bottom and then just follow the rule and use the rules to count the number of significant figures. The first number I have here is 500. Rule number 1 says the farthest left non-zero number is the most significant figure. When it says most significant figure, it just means the digit that represents the largest number that is also a significant figure. Here I can see that the 5 is the farthest left digit that is non-zero. That means that it's the most significant figure, and therefore it's also a significant figure. So I'm going to mark it with this symbol. The blue dot means it's the most significant figure, and the red dot just means that it is also a significant figure. Rule 2 says if there is no decimal point, the farthest right non-zero digit is the least significant figure. And I can see that I do not have a decimal point, so this rule does apply. So if the other two numbers are both zeros, the farthest right non-zero digit is actually also 5, so that number is also the least significant figure. Rule number 3 says if there is a decimal point, the farthest right number is the least significant figure, even if it is a 0. That would apply if we had a decimal point, but we don't, so we're going to skip that rule. And all numbers between the most significant figure and the least significant figure are also significant figures. And again, this rule would apply, but there are no numbers between the most and least significant figure, because that's actually the same number. So we followed all 4 rules, and I can see that there's only one number that actually is labeled as a significant figure, so that 5 is the only significant figure in the number. So there's only one significant figure in the number 500. I'm now going to do the same thing, but this time the 500 has a decimal point. Following rule number 1, the farthest left non-zero number is the most significant figure, so that means the 5 is the most significant figure again. This rule applies if there is no decimal point, but here we do have a decimal point, so I'll skip that rule. If there is a decimal point, the farthest right number is the least significant figure, even if it is a 0. So here, because I do have a decimal point, the farthest right 0 is the least significant figure. And all numbers between the most significant and least significant figure are also significant figures. So I have one number between those other two numbers, so that is going to be my other significant figure. So now this number has 3 significant figures instead of 1. So that decimal changed which numbers count as significant. We have a much longer number here. Again, I'll just follow those steps. The farthest left non-zero number is the most significant figure, so that's 7 here. If there's no decimal point, the farthest right non-zero digit is the least significant figure. This rule applies because there's no decimal point. So I'm going to go as far right as I can without just hitting a 0. And that's going to be this 2 right here. The only other number after that is a 0, so we ignore that. So this is the farthest right non-zero digit, so that is the least significant figure. This rule applies if there is a decimal point, but there is not, so we ignore it. All numbers between the most significant and least significant figure are also significant figures, so every one of these other numbers is also significant, even the zeros, because they're all between the most and least significant figure. So here I can see there are 6 significant figures in this number. Here's another number, 80.040. Again, the largest left non-zero number is the most significant figure, so that's going to be this 8. This rule applies if there's no decimal point, but here there is a decimal point, so I'll skip it. If there is a decimal point, the farthest right number is the least significant figure, even if it is a 0. So the farthest right number is over here, and it's a 0, but that's okay because the rule says it's okay, so that is the least significant figure. And all numbers between the most and least significant figures are also significant figures, so all of these numbers are also significant, so this number has 5 significant figures. Here's another one. The farthest left non-zero number is the most significant figure, so here that's going to be this 4. All the numbers to the left of it are 0, so they don't count. So that's the most significant figure. This rule only applies if there's no decimal point, and here there is. Rule number 3 says the farthest right number is the least significant figure, even if it is a 0, as long as we have a decimal point. So this 0 over here is the farthest right, so that is the least significant figure. And all the numbers in between those two are also significant figures. So there are 4 significant figures in this number. For numbers in scientific notation, only count numbers in the coefficient as significant. The power of 10 does not add to the significant figures. So here in scientific notation, I can see that this is the farthest left non-zero number, so that's the most significant. This rule doesn't apply. This rule says the farthest right digit is the least significant figure, so that's going to be this 8. And all the digits in between are also significant figures. So the power of 10 does not contribute to the number of significant figures. So here the number of significant figures is 3. That's how you apply those rules to find the number of significant figures in a number. This lecture is about how to do calculations with significant figures. I'll go over how to correctly record significant figures in your answer when you're performing addition and subtraction, multiplication and division, and I'll also go over powers and roots. When you're adding or subtracting numbers, you have to always round the answer to the same number of decimal places as the value with its rightmost significant figure in the greatest decimal place. So I'll give you a few examples of what that means. In problem number 1, I have 4.03 plus 5.4. If I look at the rightmost significant figure of both numbers, in the first number, it's in the hundredths place, and in the second number, it's in the tenths place. The tenths place is greater than the hundredths place, so I'm going to have to round my answer to the tenths place. So when I add these together, I get 9.43, and rounding to the tenths place gets me 9.4. So that would be the correct way of recording that result, and respecting the significant figures. In problem 2, I have 510 minus 418, and you'll remember that because we don't have a decimal, that's 0 and 510 doesn't count as significant. So because that's bigger than the ones place where the 8 is at, that will be the place where I round to when I do the subtraction. So I subtract, and then I round to the tens place, which gives me 90. In problem 3, I do have a decimal point in both numbers, so those zeros in 4300 are significant. So I'm going to have to round to the ones place in my answer, which gets me 4418. In problem 4, the first number goes down to the thousandths place, and the second number goes down to the hundredths place, so I need to round to the hundredths place. So I need to round to this, which gets me 0.06. Problem 5 is written in scientific notation, so I'm just going to rewrite that just so I can see a little bit more clearly which decimal place each number goes to. I can see that the left number goes to the tens place, and the right number goes to the hundredths place, so I'll round to the hundredths place. Problem 6 is also in scientific notation, and if I want to rewrite that in scientific notation, this is how it would look. In problem 6, I'm subtracting two numbers in scientific notation, and I'll rewrite them so it's a little more clear. So I can see that first number is in the hundredths spot, and the second number is in the hundredths spot, so I'll round to the hundredths spot. So that would be my answer. Moving on to multiplication and division, the rule works a little differently. When you're multiplying or dividing two numbers with significant figures, you have to round the answer to the same number of significant figures as the value in the problem with the least number of significant figures. So I no longer care about the decimal place, I only care about the number of significant figures, and I'll always round to the least number. In problem number 1, the first number has 3 sig figs and the second number only has 1, so I need to round my answer to only have one significant figure, because that's the lower number of sig figs. So when I round that, that comes out to be 60. Problem 2 is division, and I have 4 sig figs in my numerator, and because that decimal point is there in the 30, I have 2 sig figs in my denominator. So I have to round the answer to 2 significant figures, so that would be the answer. In problem 3, I have a number with 2 sig figs and a problem with 3 sig figs, because again, that decimal point is there. So that means I have to round this number to 2 significant figures. So this could be 440 with a decimal point after, but the problem is that that decimal point is making that 0 significant. So I actually have to remove that decimal point so that the 0 is no longer significant and I only have 2 significant figures. In problem number 4, I have 2 sig figs over 3 sig figs, so I'll round to 2. In problem number 5, I have 3 sig figs times 5 sig figs, so I'll round to 3 significant figures. Finally, in problem 6, we're doing a division where we have 4 significant figures over 4 significant figures, so my answer will also have 4 significant figures. So this will be my answer. Rounding that to 4 sig figs gets me 0.8978. So that's how you do multiplication and division while respecting significant figures. Finally, we can go on to powers and roots. The rule here is to round the answer to the same number of significant figures as the number being raised to the power or root. So we'll go through the examples. In example 1, I have a number with 3 significant figures being raised to the 4th. So I raise it to the 4th power, and then round it to 3 significant figures, and this is what I get. In problem number 2, I have a number with two significant figures, and we're taking the square root. So I know that the square root of 16 is 4, but my answer has to have two significant figures in it. So to add more significant figures, I'm going to rewrite this number as 4.0. That would be the correct way of writing it so that it still has the same number of significant figures as the original number. In problem 3, this problem has three significant figures. So raising that to the third gets me this, and I'll round it to three significant figures, and this is my answer. In problem number 4, this number only has one significant figure, so when I take the square root, I have to round this to just one significant figure as well. Number 5, we have four significant figures, so rounding that gets me this answer. And in problem 6, I have two significant figures, so taking the cubic root gets me 2.1 times 10 squared. So that's how you do calculations while respecting significant figures. In this lecture, I'll introduce the idea of variables, units, and prefixes. A variable is a quantity that can change its value, and a unit is a definite magnitude or quantity that is used to measure the same type of quantity. Our normal way of writing numbers in physics is to say that a variable is equal to a number times a unit. So we could say the weight of an object is 35 pounds, that means 35 times 1 pound. Time is equal to 20 seconds, distance is equal to 5 miles. So the unit is always written to the right of the number. Units are there to give meaning to the numbers that we use in equations, and without units, we wouldn't have any way of understanding what our numbers meant. As an example, I could say I ran for 5, but that doesn't really tell you anything, because that could mean I ran for 5 seconds, or 5 minutes, or 5 hours, or maybe for 5 miles. So you don't even know if that's a unit of time or a unit of distance. Putting a unit next to the number gives the number meaning that it wouldn't have if it didn't have a unit. So the units tell us what these numbers are measuring. Units written next to numbers mean the unit is being multiplied by the number. In equations, units behave exactly like numbers being multiplied by the value they're written next to. So as an example, if I multiply 10 kilograms times 5 meters, I get 50 kilogram meters. And that can only really be true if we consider the units to be multiplied by the numbers they're next to. So you can see on the right they behave just like numbers being multiplied, where if I have 10 times 3 times 5 times 2, that's equal to 50 times 3 times 2. So if you replace the units with regular numbers, the same operation works. And if you divide two numbers with units, the units themselves get divided, just like they would if they were just regular numbers being multiplied by their number. If you raise numbers with units to a power, the unit also gets raised to that same power. So 10 meters cubed is equal to 10 cubed meters cubed. And in this way, units also behave the same as numbers being multiplied, because 10 times 4 cubed is equal to 10 cubed times 4 cubed. We can only add or subtract numbers that have the same unit. So 10 kilograms plus 5 kilograms is equal to 15 kilograms, and that makes sense. But 10 kilograms plus 5 meters is not equal to 15 kilogram meters. There's actually no answer to that problem. And in the same way, we can only add or subtract numbers that are multiplied by the same number. So if I add 10 times 3 plus 5 times 3, I know that that's equal to 15 times 3. But if I wanted to calculate 10 times 3 plus 5 times 2, that would not be equal to 15 times 3 times 2. It would equal a different value. So you can only add or subtract numbers that have the same unit. In IB physics specifically, we do not write units in numerators and denominators of fractions. Instead, we write them as having positive or negative powers. And just remember, what a negative power physically means is just 1 over that positive power. So 1 over x to the power of a is equal to x to the power of negative a. I have this example problem here where I'm multiplying and dividing these numbers, and I'm going to show you the correct way that we would write the result and the unit in IB physics specifically. So when I combine the numbers together and combine the units together, this is what I get. So I'm dividing 160 over 10, and I'm dividing those units in the numerator by the denominator. So I'm going to rewrite the units as having powers instead of being in a numerator or denominator. So that m in the denominator is canceled out by the m cubed in the numerator, and I'm just left with m squared. And a squared is still in the denominator, so I rewrite that as a to the power of negative 2. That just means that it's in the denominator squared. So that way of writing a unit on the bottom right is the way that we would record that unit in IB, rather than recording it as a fraction. This makes it easier to do math with units in more complicated problems. In physics, we are only going to use SI units. SI stands for Système International, which is French for the International System. SI units are the internationally agreed upon system of units which all scientists in the world use. SI units are the modern form of the metric system, and they were designed specifically to be easy to use in science. So just to compare what you might normally use in the United States to an SI unit, in the imperial system, which most people in the United States use, we measure length in feet, whereas in SI units, we measure it in meters. We measure force in pounds. SI units were very specifically designed to be very, very easy to use in calculations. In an SI unit, 1 kilometer is equal to 1,000 meters, so that's a very easy to understand number, whereas in imperial units, 1 mile is equal to 5,280 feet, which is much more difficult to remember and do calculations with. So SI units were very specifically designed to be easy to use in science. There are only 7 fundamental SI units. You can see that I have them listed on the right: the meter, the kilogram, the second, the Kelvin, the mole, the ampere, and the candela. These are units that we can combine with each other to make all other units of measurement. So all units that we will use this year in physics are actually just combinations of these 7 basic units. Units that are not fundamental are called derived units. I'll give you a quick example of what a derived unit looks like. In physics, we measure force in units of capital N, which stands for a Newton. But this unit is actually made up of the fundamental units, because force is equal to mass times acceleration, and if you don't know that, that's fine. I'm just giving you an example, so I'm just going to have you follow along what I'm saying. And acceleration is equal to a change in velocity over time, and velocity is equal to a length traveled over time. So because velocity is length, which is measured in meters, over time, which is measured in seconds, the unit of velocity is a meter per second, or a meter times second to the power of -1. And because acceleration is velocity over time, that means the unit of acceleration is the unit of velocity over the unit of time, which is equal to a meter per second squared. And so the unit of force is equal to the unit of mass times the unit of acceleration. And the unit of mass, as I can see on my table, is a kilogram. So the unit of force is a kilogram meter per second squared. And I know that it's also equal to a Newton. So a Newton is actually just a stand-in for a kilogram meter per second squared, so it's a derived unit. It's a unit that's actually made up of the fundamental units. So that's what I mean by a fundamental versus a derived unit. SI units can have prefixes, which are symbols at the beginning of the unit, which change the size of the unit. I have the main prefixes that we use listed on the left. Giga means 10 to the power of 9, mega means 10 to the power of 6, kilo means 10 to the power of 3rd, and you can read the rest. If I put one of these prefixes or one of these letters at the front of a unit, that multiplies the value of the unit by the value that I've listed in the table. As an example, a kilometer is equal to 10 to the 3rd meters. So kilo is kind of taking the place of 10 to the 3rd there. It means the same thing. So a kilometer is 10 to the 3rd meters, or km is equal to 10 to the 3rd m. A megameter would be 10 to the 6th meters, and a gigameter would be 10 to the 9th meters. And we can also go in the opposite direction, where a centimeter is 10 to the power of -2 meters, and a millimeter is 10 to the power of -3 meters, a micrometer is 10 to the power of -6 meters, and a nanometer is 10 to the power of -9 meters. So those prefixes take the place of those numbers and tell us how big or small the unit is. Notice that the kilogram is the only fundamental unit with a prefix. Scientists chose the kilogram as the fundamental unit for mass instead of the gram because a kilogram is closer in magnitude to everyday objects. It's about 2.2 pounds. So that's all the basic information that you need to know about variables, units, and prefixes. We're going to return to these concepts a lot throughout the year, and at the end of the course, we'll be able to reduce all of the units that were given to the 7 fundamental SI units. This lecture is going to be a series of examples of reducing derived units to fundamental SI units in physics, and this lecture is going to assume that you are familiar with the main IB physics variables. This is made to be watched toward the end of a physics course. So I have my 7 fundamental SI units written on the right. And because these are the only 7 fundamental units, it's possible to rewrite any other unit in terms of just those 7 units. So the 6 units that I have listed on the left are all examples of derived units. They're actually just placeholders for combinations of the 7 fundamental units. I'm going to go through each individual unit and understand which fundamental SI units make it up. And to understand their relationship, I'm going to look for equations that I know that connect more complicated ideas like, say, force to more simple ideas like mass and acceleration. So we know that a Newton relates to force, and force is equal to mass times acceleration. And that means that a newton is equal to a unit of mass times a unit of acceleration. And the unit of mass is a kilogram, and the unit of acceleration is a meter per second squared. So a newton is actually equal to a kilogram meter per second squared. So that's a newton expressed in terms of the fundamental SI units. I remember that a Pascal is a unit of pressure, and pressure is equal to force over area. So that means that a Pascal is equal to a unit of force, which I know from the previous problem is a kilogram meter per second squared, over a unit for area, which is a meter squared. And when I divide those out, I get a kilogram meter to the -1 seconds to the -2. So a Pascal is taking the place of those fundamental SI units. Because there are different equations for energy, there are different ways I can understand the meaning of a joule. I'll start with the kinetic energy equation. I know that energy is equal to 1/2 mv squared, and a joule is a unit of energy. So a joule is also equal to a unit of mass times a unit of velocity squared. The 1/2 there does not have a unit. So when I multiply that out, I get that a joule is equal to a kilogram meter squared per second squared. I could also do a calculation with another energy equation, like gravitational potential is equal to mgh. And I know that the unit of mass is a kilogram, and lowercase g is the acceleration of gravity, so that has a unit of acceleration, which is a meter per second squared. And the height has a unit of meters, and when I multiply those out, I find that I get the same value, a kilogram meter squared per second squared, which makes sense if I'm expecting this to be equal to a joule. So that's a joule expressed in fundamental units. A watt is a unit of power, which is equal to the change in energy over time. So a watt will be equal to the unit of energy, which I can take from problem 3, over a unit of time, which is a second. And when I divide that out, I get a kilogram meter squared second to the -3rd. Moving on, I know that voltage is equal to the electric field value times the distance that a particle travels through the field. And I know that the unit of the electric field is a newton per coulomb, and the unit for distance is meters. So a volt is equal to a newton per coulomb times a meter. And I know the fundamental units for newtons, so I'll replace that. And I need to know what a coulomb is in terms of the fundamental units. I know that current is equal to charge per time. So that means that charge is equal to current times time. So that means that a coulomb is equal to an amp or an ampere multiplied by the unit for time, which is seconds. And as you can see on the right, the amp is a fundamental unit. So I can replace a coulomb with an ampere second. And when I multiply that out, I get a kilogram meter squared per second cubed per ampere. Finally, I know that an ohm is a unit of resistance, and resistance is voltage over current. So I know that an ohm is equal to the fundamental units for voltage over the unit for current, which is just an amp. So that's equal to a kilogram meter squared per second cubed per ampere squared. And I also know that resistance is equal to power over current squared. So I could also take my unit for power, the watt, and divide it by amperes squared. And when I do that, I see I get the same fundamental units for an ohm. So that's how you rewrite derived units in terms of fundamental units in physics. In this lecture, I'll show you how to convert units using the factor label method. When I say convert a unit, what I mean is to take a measurement, like for example 6 feet, and to convert the measurement to a new unit without changing the true real value of the measurement itself. As an example, if I wanted to know how tall this person was in inches, I know that 1 foot is equal to 12 inches. So if I multiply 6 feet times 12 inches per foot, I get 72 inches. So these two measurements represent the same value, they're just written with different units. And because they're written with different units, they also have to be written with different numbers to make the two things equal. I can't just change the unit without also changing the number in some way, because 72 inches is not equal to 72 feet. So I need some way of knowing how to change a measurement from one unit to another unit without changing the true value of the measurement itself. The method that we use for converting units in this class is the factor label method. I've listed the 3 steps of the method here, so I'm going to take you through each step as I do 5 example problems to show you how it works. Example problem 1 says to convert 3,500 meters to kilometers. So I'll start with my original measurement that I want to change. Step number 1 says to multiply the number by a fraction with the unit that you want to get rid of in the part of the fraction that will cancel it out. So I want to get rid of meters, so I'm going to write a fraction and multiply it by my number. And because meters is in the numerator of my original number, if I put it in the denominator of my fraction, that will cancel it out. Step 2 says to write the new unit you would like to add in the opposite part of the fraction as the unit you want to get rid of. So I want kilometers in my final answer, so I'm going to put that in the numerator, which is the opposite part of the fraction as where I put meters. Step number 3 says to choose a number to put in the numerator and a number to put in the denominator so that the numerator and denominator are equal. I'll explain why we take this step in the final part of the video, but for now I'll just think about what two numbers would make these equal. I know that in every 1 kilometer there are 1,000 meters. The K actually stands for 1,000 or 10 to the third. So if I write 1 kilometer and 1,000 meters, those two numbers make the numerator and denominator equal to each other. So that's how you do the third step. I could have chosen other numbers. I could have chosen 2 kilometers over 2,000 meters or 0.001 kilometers over 1 meter. Any two numbers that make the numerator and denominator equal are okay. Finally, I just have to multiply this out, and when I multiply the number by the fraction, the meters cancel out because one's in the numerator and the other's in the denominator, and I'm left with 3,500 times 1 over 1,000 kilometers, which is equal to 3.5 kilometers. So 3,500 meters is equal to 3.5 kilometers, so I've converted the unit without changing the actual real value of the measurement. And that's how you use the factor label method. Example number 2 says to convert 50 kilometers per hour to meters per second. This will involve several steps. So we'll start with my original measurement. I've just added another sig fig there, just so my final answer can also have 3 sig figs. Step number 1 says to multiply the number by a fraction with the unit that you want to get rid of in the part of the fraction that will cancel it out. And I actually have 2 different units that I want to get rid of here. So I'm actually going to multiply by multiple fractions and just focus on 1 unit at a time. I'll start by focusing on kilometers. So because kilometers is in my numerator, I'll put it in my denominator. And I want meters in my answer, and I want that in the numerator, so I'll put that in the numerator. And now I just need to choose numbers that make those two things equal, and I know that there are 1,000 meters in every 1 kilometer. So I've successfully removed kilometers and added meters. But I still have hours in my denominator, and I need to convert that to seconds in the denominator. So I'll write a second fraction. And because hours is in my denominator and I want to cancel it out, I need to put it in the numerator of my new fraction. And I'll pretend that I don't know how many seconds are in an hour and just go from hours down to minutes just to reduce the time a little bit. And then I'll be able to get from minutes to seconds. I know that for every 1 hour there are 60 minutes, so that cancels out hours. And then I can write one more fraction where I go from minutes to seconds. And for every 1 minute there are 60 seconds. So that cancels out minutes, and now the only units that are remaining are meters in the numerator and seconds in the denominator, which is what I want. So 50 kilometers per hour is equal to 50 times 1,000 over 1 times 1 over 60 times 1 over 60 meters per second, which is equal to 13.9 meters per second. So if you have multiple units that you need to convert, you just focus on converting 1 unit at a time. Example number 3 says convert 3 years to seconds. So I start with 3 years. And I don't know how many seconds are in a year, but I can make the time smaller and smaller until I get to seconds, because I know how many days are in a year. So I'll put days in my numerator and years in my denominator. For every 1 year, there's 365 days. And I also know how many hours are in a day. For every 1 day, there are 24 hours. And I also know how many minutes are in an hour. And I know how many seconds are in a minute. So this is telling me that 3 years is equal to 3 times 365 over 1 times 24 over 1 times 60 over 1 times 60 over 1 seconds. And when I multiply that out, this is the answer that I get. I'm ignoring significant figures for this one. Example 4 says the volume of 1 bus is equal to 12 cars, 3 cars is equal to 1 truck, and 1,000 basketballs equals 1 truck. How many basketballs can be carried by 8 buses? So I'm going to take 8 buses and convert that to units of basketballs. So I can go from buses to cars because I have a connection there, and the problem says that for every 1 bus, we can fit 12 cars. And I can then go from cars to trucks because there's a connection there. For every 1 truck, there are 3 cars. And I can go from trucks to basketballs because I have an equivalency there as well. And when I multiply that out, I get 32,000 basketballs. Example number 5 says how many millimeters are in 2 megameters. I'm using this as an example of converting from one prefix to another prefix. So if you have 2 megameters, I'm first going to convert from megameters down to meters because I know the relationship there. For every 1 megameter, I know that the mega is standing for 10 to the 6th. So for every 1 megameter, there's 10 to the 6th meters. And then I can go from meters down to millimeters because I know that 1 millimeter is equal to 10 to the minus third meters. So those cancel out. And when I multiply out those fractions, I get 2 times 10 to the ninth millimeters. We call each individual fraction here a conversion factor because we're using it to convert from one unit to another. The reason this method works is that each conversion factor is equal to 1 because the numerator equals the denominator, so multiplying by the conversion factor does not change the actual value of the number, but does change the unit. So no matter how many times you multiply by 1, you always get the same result. So that's why the factor label method works, and that's how you use it to convert from one unit to another. In this lecture, I'll go over the 4 main proportional relationships that we deal with in IB physics, which are linear, quadratic, inverse, and inverse square relationships. I'll start off with the notation that we use. That symbol that looks kind of like a fish means is proportional to. So if you see notation like what I have below, y, that notation means y is proportional to x. What it means for something to be proportional to something else is that that one thing is equal to a constant multiplied by the other thing. So here y is proportional to x means that y is equal to some constant multiplied by x. We use the symbol when we don't know the value of the constant and are really just worried about the relationship between y and x. One implication of this definition is if y is proportional to x, x is proportional to y. Because if y is equal to a constant times x, that means that x is equal to 1 over that constant times y. And this is just another constant. 1 over a constant is itself a constant, so that means that x is also equal to a constant times y. So we could say that x is proportional to y. So if y is proportional to x, x is proportional to y. These are the 4 main proportional relationships that we worry about in IB physics. There are others as well, but we mainly focus on these when we're analyzing proportionality. In a linear relationship between 2 variables, y is proportional to x. And you can see that results in a straight line linear graph when we graph y against x. In a quadratic relationship, y is proportional to x squared, which means that y is equal to some constant times x squared. And you can see the shape of a quadratic equation that happens when we graph y versus x in that situation. In an inverse relationship, y is proportional to 1 over x, and you can see the graph for that. And in an inverse square relationship, y is proportional to 1 over x squared. And you can see we have the shape of that graph as well. So one thing knowing these patterns allows us to do is to take the relationship between 2 variables in an equation and understand exactly what the graph of those 2 variables would look like if we held everything else constant. I'll give you a bunch of examples of what using these physically looks like in problem solving. To identify the proportional relationship between 2 variables in an equation, hold all other variables constant and match the resulting equation to one of the 4 relationships. If both variables appear on one side of the equation, rearrange the equation so that one variable is on each side. In this first example, it's asking, given this equation, what is the relationship between force and acceleration, and what is the shape of a force versus acceleration graph? Because we're only worried about force and acceleration, the rule says to hold all other variables constant, so m is going to be a constant here. I'll treat f as my y and a as my x. This fits the form y equals some constant times x, and that implies that y is proportional to x. So in the same way, we can understand that f is proportional to a. Force is proportional to acceleration. So what we get from this pattern is that force has a linear relationship with acceleration. Because if we go back to this chart, we can see that if 2 variables are proportional to just each other with no square or no denominator, they exist in a linear relationship with each other. So force has a linear relationship to acceleration. We can also see based on the equation that force is proportional to acceleration. And because this fits a linear pattern, I know that the graph of force versus acceleration is also going to be linear. So just using the shape of the equation, I can automatically understand what the graph of those 2 variables will look like. So that's why we care about these proportional relationships. We can talk about the relationship between 2 variables and understand how the resulting graph of the 2 will look. Example number 2 says, given this equation, what is the relationship between mass and acceleration, and what is the shape of a mass versus acceleration graph? So here we're going to hold force constant, so we're imagining we have a constant force in this situation. So I'll isolate mass by dividing both sides by acceleration. And when I do that, I find that the equation fits this form, y is equal to a constant times 1 over x, which means that y is proportional to 1 over x. So I can see that the mass is proportional to 1 over acceleration, and that tells us that this relationship is inverse. Mass has an inverse relationship with acceleration, and mass is proportional to 1 over acceleration. And because this is an inverse pattern, I know automatically that the graph of mass versus acceleration is going to look like this. It will have the shape of an inverse graph when we plot those two variables. Example problem 3 says, given this equation, what is the relationship between the gravitational field and the distance from the source? I can see that gravitational field is lowercase g, and the distance from the source is r, so I'm going to have to hold the other two things constant in that equation. I'll rearrange this just a little bit just to draw out 1 over r squared. And when I do that, I can see that this fits the form y equals some constant times 1 over x squared, which means that y is proportional to 1 over x squared, which means that the gravitational field is proportional to 1 over the distance from the source squared. So what this tells us is that the gravitational field has an inverse square relationship with the distance, and the gravitational field is proportional to 1 over distance from the source squared. And because this is an inverse square relationship, we know automatically that the graph of gravitational field versus the distance from the source will take this general shape. Example 4 says, given this equation, what is the relationship between the gravitational field and the mass? So I'll hold capital G and r squared constant. I'll rearrange the equation just to get the mass by itself. I can see that the gravitational field is proportional to the mass, which tells us that the gravitational field has a linear relationship with mass, and the gravitational field is proportional to mass. And this is what a graph of gravitational field versus mass would look like. Finally, example 5 says, given this equation, what is the relationship between the mass and the distance from the source? So now I need to isolate m and r squared, so I'll hold lowercase and uppercase g constant. So I'll rearrange the equation to get one of those variables by itself. I'll just get mass by itself. When I generalize this, I see that this fits the form y equals a constant times x squared. So that means that y is proportional to x squared, and mass is proportional to r squared. So what we get from this is the mass has a quadratic relationship with distance, and the mass is proportional to distance squared. So this is the mass versus distance from source graph, and it fits a quadratic pattern. We can also find the mathematical relationship between variables by looking at the pattern on a graph of both variables, assuming other variables are held constant. As an example, I can see that momentum has a linear relationship with velocity, which means that momentum is proportional to just velocity without anything being done to it. So this is the information I can get just looking at that graph. When I look at the kinetic energy versus velocity graph, I can see that that's a quadratic pattern, so I know that kinetic energy is proportional to velocity squared. So that's the information I can get from that graph. When I look at resistance versus current, I can see that that relationship is inverse. So therefore, the resistance is proportional to 1 over the current, and that's the information I have. And when I look at a graph of an electric field over distance, that's an inverse square relationship. So I know that the electric field is proportional to 1 over the distance squared, and the electric field has an inverse square relationship with distance. So that's how you use proportional relationships along with the patterns that show up in graphs to get more information about the relationships between different variables in physics. In this first lecture on uncertainty, I'm going to introduce the notation that we use and why the notation represents a range of possible values. We use a specific notation to write how uncertain we are about a measurement. Here I have it written a plus or minus delta a, but it can be any letter. It could be b or c or d plus or minus delta b or c or d. These symbols have specific meanings. This is the actual number value of our measurement, and this is the uncertainty of our measurement. What these symbols physically represent is that we have some measurement A, but we're not sure that the measurement is at that exact value. It could be delta A smaller than A, so the smallest possible value would be A minus delta A, or it could be delta A larger than A, so the largest possible value would be A plus delta A. So this means that the actual value of our measurement could be anywhere within this range from A minus delta A to A plus delta A. And so that's why we use the symbol plus or minus delta A when we're dealing with uncertainty. So we say that this notation represents a range of possible values. It's a range of numbers that our measurement could be inside because we're unsure about the exact value of our measurement, so it could be anywhere within that range labeled by A plus or minus delta A. So those variables represent the general notation that we use, but we can also have specific notation where we write the exact numbers and uncertainties. For example, we could have a measurement that's 5 plus or minus 3. What that would mean is that the measurement would have the value 5, but we're uncertain about it. So it could be as low as 5 minus 3, which is 2, Or the actual value of the measurement could be as high as 5 plus 3, which is 8. So the actual true value of that measurement could fall anywhere along this range of possible values. It could be anywhere from 2 to 8. That's what that 5 plus or minus 3 physically represents. So any number within that range is a possible value here. Numbers like 2 or 3.14159 and 7 are all possible values, whereas 1 or 8.001 are not possible values because they fall outside that range of possible values. So that's physically what that symbol 5 plus or minus 3 represents. It could mean that our actual measurement could fall anywhere along the range 5 minus 3 to 5 plus 3. If you're given a range and asked to write the range as a number with uncertainty, you can use this method, where the number value is equal to the max plus the min of the range over 2. This is also the average of the range. And the uncertainty is equal to the max minus the min over 2. That's the range value divided by 2. So I can see that A takes the exact middle point between the max and the min, so that's why it's the average. And delta A is the range divided by 2. For example, I could say I have a range from 2 to 8, and I want to know how to write that with this new uncertainty notation. So we know that the number value is the average of the maximum and minimum, which is equal to 5. And the uncertainty is the maximum minus the minimum divided by 2, the range divided by 2, which I can see is equal to 3. So that means that this range of possible values can be written as 5 plus or minus 3. I'm going to close the video with example problems where we write the uncertainties as a maximum and minimum range and write the maximum and minimum range as a number with uncertainty. So I'm going to let you try this. I'll pause the video and see if you can write each uncertainty as the maximum and minimum range, and then write the maximum and minimum range as a number with uncertainty. And remember, those two things mean the same thing. They're just two different ways of recording it. So these are the ranges that are indicated by the numbers with uncertainty, and these are the numbers with uncertainty that are indicated by the ranges. And that's what you have to know about the basics of uncertainty notation and the range of possible values. This lecture is about the definition and difference between absolute, fractional, and percent uncertainty. Absolute uncertainty is uncertainty expressed as a number independent of the original number. The symbol we use for absolute uncertainty is the symbol delta, and then the letter variable for what we're measuring. Fractional uncertainty is uncertainty expressed as a fraction of the original number, is delta and then the variable over the original variable. I'll explain why that is in a moment. And percent uncertainty is uncertainty expressed as a percentage of the original number. And you can see I have that symbol and equation written there. I'll give you a visual to understand the difference between each of these. Let's say that we have 4 plus or minus 1. What this would look like on the number line is we have the number 4, but the actual value of this measurement could be as high as 4 minus 1 or 4 plus 1. So the red line indicates the value of the measurement and the blue line indicates the value of the uncertainty. I can understand how big that uncertainty is without referring to the 4. I can understand that no matter how big the red number is, the uncertainty itself is going to be plus or minus 1. It'll go up 1 and down 1. So because that number is independent of the measurement number, that uncertainty is expressed as an absolute uncertainty. I'm going to write the same number and uncertainty, but with fractional uncertainty. I need to understand what fraction the uncertainty is of the number. And I can see here that 1/4 of my number is uncertain. 1/4 of my total measurement I'm uncertain about. It's not that full range from 3 to 5, it's not 2 over 4. It's half of the range because that's how we usually express uncertainty, as half of the full range. So 1/4 of my measurement is uncertain. So that fraction expressed as a decimal is 0.25. So 0.25 times my measurement is uncertain. So this is how I would express that uncertainty with fractional uncertainty. This is the uncertainty expressed as a fraction of my original number. And percent uncertainty is uncertainty expressed as a percentage of the original number. And if 1/4 of my measurement is uncertain, that means 25% of my measurement is uncertain. You can see that these expressions all express the same uncertainty. They're all referring to that same red and blue line. They're just different ways of writing that same uncertainty. So absolute, fractional, and percent uncertainty are 3 different ways of recording the same fundamental thing. And you can see now why the equations work in the way that they do. because the fractional uncertainty is the absolute uncertainty, delta A, divided by the original number A. In my case, it was 1 over 4. And the percent uncertainty is that fractional uncertainty multiplied by 100%. 25% is 0.25 times 100%. These equations will always work to convert from one uncertainty to another. In comparison to absolute uncertainty, we call fractional and percent uncertainty relative uncertainty, because the value of the uncertainty is relative to the value of the measurement. So with absolute uncertainty, even if I don't know what the measurement is, I can still understand the exact size of the uncertainty. Here it's just plus or minus 1. That's absolute on its own, so I can understand it independently of any other number. But for fractional and percent uncertainty, if I can't see the original measurement, I don't actually know how large that is. So if I'm dealing with 25% of 1, that's going to be a very different size of uncertainty compared to 25% of 100. So the actual physical size of the uncertainty is relative to the original measurement in a way that it's not with absolute uncertainty. So we say that fractional and percent uncertainties are both examples of relative uncertainty for that reason. These are instructions for converting between each type of uncertainty. When you're going from absolute to fractional, you divide the absolute uncertainty by the number. When you're going from fractional to percent uncertainty, you multiply the fractional uncertainty by 100%. And in the other direction, if we're going from percent to fractional uncertainty, you divide by 100%. And from fractional to absolute uncertainty means you multiply the fraction by the number. The unit of measurement is written in a different place for absolute, fractional, and percent uncertainty. For absolute uncertainty, it's written to the far right of the number, because both of those numbers are measurements in that unit. They're both independent of each other and absolute, so they're both measuring amounts of that unit. Whereas with fractional and percent uncertainty, we put the unit only next to the measurement value, not next to the uncertainty, because that uncertainty is not actually measured in the same units as the original number. It's some fraction or percentage of that original number, so we're not using the same units for it. As an example, if we were measuring something in kilograms, this is how we would write the absolute, fractional, and percent uncertainty with the unit in the correct place. And just looking at the bottom right, it wouldn't really make sense to say, oh, this is plus or minus 25% kilograms. Like, that statement on its own doesn't really make sense. So we say instead that it's 4 kilograms plus or minus 25% of that value. The placement of the unit can tell us whether the uncertainty is absolute or fractional. You can definitely have decimal uncertainties that are absolute. So a way of understanding whether those uncertainties are absolute or fractional is to look at where the unit is in the measurement. If it's an absolute uncertainty, the unit occurs after the number and uncertainty, but if it's a fractional uncertainty, the unit is only written after the number, not after the uncertainty. There are rules for decimal places in absolute uncertainty, but not really rules for fractional and percent uncertainty. If the absolute uncertainty goes to more decimal places than the number, the uncertainty is rounded to the same number of decimal places as that number. And if the number goes to more decimal places than the absolute uncertainty, the number is rounded to the same number of decimal places as the uncertainty. So the lowest decimal place of both the number and the uncertainty always have to match. And you always round up the value that goes to the lowest decimal place. There are no clear rules for recording significant figures or decimal places in fractional and percent uncertainty. The amount of significant figures you record will usually be told to you in the problem. And if you're not told about them, it's okay to write the number of sig figs that you would like, because the problem isn't being clear enough on its own. The rest of the video will just be example problems where I convert between different types of uncertainty, using the rules that I introduced earlier. I'm going to start by converting each absolute uncertainty to fractional uncertainty. So to do that, I divide each absolute uncertainty by its original number and rewrite it as a decimal. And I can now rewrite these values with fractional uncertainties, so the numbers stay the same, the unit is moved next to the number, and I'm now writing in the fractional instead of the absolute uncertainties. Going to the right, to convert each fractional uncertainty to absolute uncertainty, I multiply the fraction by the original number, and when I do that, I get the absolute uncertainty for each number. And you'll notice that I rounded the uncertainties correctly to go to the same decimal place as the original numbers. And as a policy, we usually round absolute uncertainty to just one sig fig. So the number of places in the uncertainty must match the number of decimal places in the original number. Going down into the left, I can convert each fractional uncertainty to percent uncertainty. This is one of the easiest ones. You just have to multiply the fractional uncertainty by 100%. So this is how you would write those fractional uncertainties as percent uncertainties. And then I can convert each percent uncertainty to fractional uncertainty by just dividing by 100%. That's the rule for conversion there. I can now take two steps and convert each absolute uncertainty to percent uncertainty. So to do that, I'll convert from absolute to fractional and then from fractional to percent. So I divide the absolute uncertainty by the original number and then multiply by 100%. And this is what I get for those values. And again, I move the unit to the correct spot in each number. Finally, I'll convert each percent uncertainty to absolute uncertainty. So to do that, I can divide by 100% and then multiply by the original number. And when I do that, these are the absolute uncertainties that I get. And notice again that I'm not changing the actual value of the uncertainty, I'm just writing it in different ways in each problem. So in each problem, those answers are the same values as the others. It's just that I'm changing how I express them between absolute, fractional, and percent uncertainties, but the underlying value of each number is the same. I'll close with some rounding problems where I just round each number to the correct decimal place, and then round each uncertainty to the correct decimal place. So all I need to do is round each number to the same decimal place as its uncertainty. When I do that, this is what I get for each number. And on the right, because the uncertainties go to lower decimal places than the original numbers, I have to round those up to the lowest decimal point of each number. And when I do that, this is what I get for each uncertainty. So that's what you have to know about the definition of absolute, fractional, and percent uncertainty and how to convert between them. In this lecture, I'll show you how to propagate uncertainty when you're adding and subtracting numbers with uncertainty. The best way I know of teaching propagating uncertainty is to just give you the rule and then give you a ton of examples that I work through. So that's what I'm going to do in this video. When you're adding or subtracting numbers with uncertainty, the uncertainty of their sum or difference equals the sum of the absolute uncertainties of each individual number. So if the sum or difference y is equal to a plus or minus b, that means that the uncertainty of y, the uncertainty of that result, is equal to the sum of the absolute uncertainties of the two numbers. And just as a heads up, if you don't know what I mean by absolute uncertainty specifically, you should go back and watch my lecture on absolute, fractional, and percent uncertainty that I've linked in the description. I'll go through the 6 addition problems and then the 6 subtraction problems. In problem number 1 on the left, I can see that the uncertainties are already written as absolute uncertainties, so all I need to do is add the two numbers together and then add the two absolute uncertainties together, and this is my result. So 5 plus or minus 2 plus 8 plus or minus 4 is equal to 13 plus or minus 6. And I'm keeping that unit the same and in the correct spot. So again, if you're adding or subtracting any two numbers with uncertainty, you just add their absolute uncertainties. So I just added 2 plus 4 to get the new absolute uncertainty of 6. In number 2, we do the same thing because those are both absolute uncertainties. So I add the two numbers and then add their uncertainties together. And this is the result that I get, 9.5 plus or minus 0.8 meters. In problem number 3, we have an issue because those uncertainties are not absolute uncertainties, and I need them to be absolute uncertainties to follow the rule. So before I can add these, I need to convert these back to absolute uncertainties instead of percent uncertainties. So to do that, I just multiply the percentage as a decimal by the original number. That's how you get from percent uncertainty to absolute uncertainty. And when I do that, these are the absolute uncertainties that I get for each number. So those two numbers with uncertainty are the same as the original two numbers, they're just expressed with absolute uncertainty instead of percent uncertainty, but they're the same values. And now that they're expressed in absolute uncertainty, I can add them together using the rule, and when I do that, this is what I get. In number 4, I can see that those uncertainties are fractional uncertainties. I can tell because the unit is to the right of the number, not to the right of the uncertainty. And again, I explained how to tell that an uncertainty is fractional in the lecture linked in the description. So I have to start by converting fractional uncertainties to absolute uncertainties. So I multiply the fraction by the original number. And when I do that, this is what I get for the absolute uncertainties. And now that this is an absolute uncertainty, I can just add the uncertainties together and solve the problem. In number 5, I have a mixed problem where one of my numbers is in absolute uncertainty and another is in percent uncertainty. So I'm going to keep the absolute uncertainty the same and convert the percent uncertainty to absolute uncertainty. And when I do that, this is what I get. And then when I add the absolute uncertainties together, this is my answer. Number 6 is similar. I have a number with absolute uncertainty and a number with fractional uncertainty, so I only convert the fractional uncertainty number to be absolute. And when I do that, this is what I get. And when I add the two absolute uncertainties together, this is my result. So that's how you add two numbers with uncertainty. And if you wanted to express any of those results in fractional or percent uncertainty, you can just follow the normal rules for converting from absolute to fractional to percent. Going into the subtraction examples, when you're subtracting two numbers, you still add their absolute uncertainties to each other. A common mistake students make is to subtract them, but you still add the uncertainties. So in number 1, 10 plus or minus 2 minus 5 plus or minus 4 is going to be equal to 10 minus 5 plus or minus the sum of the absolute uncertainties. So that's going to be 5 plus or minus 6. In number 2, I follow the same rule where I subtract the numbers but add their absolute uncertainties. So the result there will be 8 plus or minus 3. In number 3, I have the numbers expressed with percent uncertainty, so I need to convert those to absolute uncertainties by multiplying the percent as a fraction times the original number. And when I do that, these are the absolute uncertainties that I get. So subtracting one number from the other and adding their absolute uncertainties gets me this answer. In number 4, I have two numbers with fractional uncertainties because of the position of the unit. So to convert from fractional to absolute, I just multiply the fraction by the original number, and then I subtract the original numbers and add their absolute uncertainties, and this is the number that I get. In number 5, I have one number with an absolute uncertainty and one number with a percent uncertainty, so I only convert the percent uncertainty to be absolute. This is what I get when I do that. And then I add the absolute uncertainties together, subtract the numbers, and this is my answer. And just notice that I rounded that uncertainty to the correct number of decimal points. Finally, in number 6, I have an absolute and a fractional uncertainty, so I convert the fractional to absolute. And this is what I get. I add the uncertainties together, and this is my result. So again, that's how you propagate uncertainty when you're adding or subtracting numbers. You add or subtract the numbers themselves, but you always add the absolute uncertainties together. And if your numbers aren't expressed with absolute uncertainty, you need to convert to absolute uncertainty before solving the problem. In this lecture, I'll show you how to propagate uncertainty when you're multiplying or dividing numbers. When you multiply or divide numbers with uncertainty, the uncertainty of their product or quotient equals the sum of the fractional uncertainties of each number. Again, just two notes before we start. First, I think the best way of introducing this idea is to just give you a ton of examples. And also, you won't understand these examples if you don't understand absolute, fractional, and percent uncertainty. So I've left my lecture on those concepts in the description of this video. I'll start with the multiplication examples. The first example is 5 plus or minus 2 kilograms times 8 plus or minus 4 kilograms. This rule says that when multiplying two numbers with uncertainty, I add their fractional uncertainty. And these two numbers I'm multiplying are listed with absolute uncertainty, so I need to start by converting that to fractional uncertainty. So that's going to be the absolute uncertainty over the original number. So this is the fractional uncertainty I have for each number. So now the rule says to multiply the two actual numbers and then add the two fractional uncertainties. So that's what I do. And when I do that, this is the answer I get. Because I multiplied a kilogram by kilogram, the unit there is a kilogram squared. So that's the process. You just have to convert the uncertainties to fractional uncertainties and then add them together, and that will be the new uncertainty of the product of those two numbers. In problem number 2, I have more numbers with absolute uncertainty that need to be fractional uncertainties. So I'll convert them to fractional uncertainties, and when I do that, these are the fractional uncertainties that I get. So the rule says to add the fractional uncertainties together, and when I do that, this is the result. I'm not so worried about significant figures here, because there's no clear rule for how many significant figures to write when you're dealing with fractional uncertainty. The numbers in problem 3 are written as percent uncertainties, and because percent uncertainties behave in basically the same way as fractional uncertainties, I can actually just add the percent uncertainties together to get the uncertainty of the result. So again, I multiply the two numbers and add the percent uncertainties. In problem 4, this is already given in fractional uncertainty, so all I have to do is add the fractional uncertainties, and this is the result that I get. In problem 5, I have one number in absolute uncertainty and another number with percent uncertainty, so I need to convert that absolute uncertainty into something I can add to the percentage. So I'll convert the percentage to a fractional uncertainty, and I'll also convert the absolute uncertainty to a fractional uncertainty by dividing it by the original number. So now I add the fractional uncertainties together and multiply the two numbers, And so this is my final answer with a fractional uncertainty. In problem number 6, I have an absolute uncertainty and a fractional uncertainty. So I convert the absolute to fractional like this, and then add the fractional uncertainties together and multiply the two numbers. And so this is the product of those two numbers with uncertainty. The division rule actually works the same way. I'm going to divide the two numbers, but I'll still add the fractional uncertainties together. Notice that I've squared all the numerator units just to make sure that the unit comes out correctly at the end. The square doesn't apply to any other part of the number except the unit. In example number 1, I have 10 plus or minus 2 divided by 5 plus or minus 4. So I convert the absolute uncertainties to fractional uncertainties. So this is what I get. The rule says to divide the two numbers and add the fractional uncertainties together. So when I do that, I get 2 plus or minus 1.0. And again, that answer is still in fractional uncertainty, so it's kind of like saying 2 plus or minus 100%. In absolute uncertainty, that would be 2 plus or minus 2. In problem 2, we have 12 plus or minus 2 over 4 plus or minus 1. So again, I start by converting to fractional uncertainty. So those are the results. And then I divide 12 by 4 and I add the fractional uncertainties together. And this is the result. In problem 3, the uncertainties are written as percent uncertainties, and because percent uncertainties behave so much like fractional uncertainties, I can actually just add those together to find the answer to my problem. So that will be the answer, because it's just the two original numbers plus or minus the sum of the fractional or percent uncertainties. In problem 4, the uncertainties are already fractional, so I just add them together. And so this is the result. In problem 5, the numerator is absolute and the denominator is a percent uncertainty. So I convert the absolute uncertainty to a fractional uncertainty and convert the percent uncertainty to a fractional uncertainty. This is what I get. And when I add them together, this is my answer. In problem number 6, I have an absolute uncertainty over a fractional uncertainty. So I convert the absolute to a fractional uncertainty. And then again, I add the fractional uncertainties together and divide the two numbers. So that'll be my answer. So that's how you propagate uncertainty when you're multiplying or dividing. You convert the uncertainty to fractional uncertainty and then add the uncertainties together to find the fractional uncertainty of the result. In this video, I'm going to show you how to propagate uncertainty with powers and roots. This is the rule that we use. When you raise a number with uncertainty to a power, and remember that a root is just a fractional power, the uncertainty of the result equals the absolute value of the product of the power and the original fractional uncertainty. So that was a lot of words, but I think you'll find that once you actually apply the rule, it's pretty simple. I'll start with power examples and then go to root examples. The first problem says we have 5 plus or minus 2 kilograms squared. And the rule is telling me that I need to do something with the fractional uncertainty. So before I solve this problem, I have to convert that number to a fractional uncertainty. And the way that I do that is dividing the absolute uncertainty by the original number. If you don't remember how to do that, I have a video in the description explaining how. So my rule is saying that the uncertainty of the result of raising this number to this power is going to be equal to the power multiplied by the fractional uncertainty. So that means the uncertainty will be 2 because that's the power multiplied by the fractional uncertainty of 0.4. And for your original number, you just apply the square to it. So when I multiply that out, I get 25 kilograms squared plus or minus 0.8, because 0.8 is 2 times 0.4. And again, that 0.8 is also a fractional uncertainty. So if you wanted to convert back to absolute uncertainty, you could just multiply that 0.8 times 25, and you would have a new absolute uncertainty that represents the same thing as the fractional uncertainty. Problem number 2 says 2.5 plus or minus 0.5 meters raised to the fourth. Again, that's an absolute uncertainty, and I need to convert it to fractional uncertainty. So I'll divide the uncertainty by the original number. So that's my fractional uncertainty. And the rule says that my new uncertainty will be the power multiplied by the fractional uncertainty. So I'm multiplying that fractional uncertainty by 4. And this is the answer that I get. Number 3 has a percent uncertainty, and because percent uncertainties behave similarly to fractional uncertainties, like 10% is just 0.1 as a fractional uncertainty, I can actually just follow that same rule and multiply the power by the percent uncertainty, and that will get me the correct answer. So 20 raised to the third is 8,000, and that'll be plus or minus 30%. In problem 4, we're raising 12 plus or minus 0.15 to the power of 7. This is already expressed in fractional uncertainty, so I just need to multiply the power by that fraction. And when I do, this is the uncertainty that I get and the number that I get. Going on to the root examples, I'll just have you look up at the top right and remember that x under a certain root is equal to x raised to the power of 1 over that root. So in the first problem, that square root or second root is the same as that number being raised to the power of 1/2. So I can now just apply my normal power rule to this problem. The power rule says that I need that uncertainty as a fractional uncertainty. So when I plug that in, this is the fractional uncertainty that I get. And then I multiply that by the power, and this is the result that I get for my uncertainty and for the original number. That's the same as 12 plus or minus 2 raised to the power of 1/4. So I need to convert that to a fractional uncertainty to follow the power rule, and when I do that, this is what I get. So I multiply the uncertainty by 1/4, I raise 12 to the power of 1/4, and this is the answer that I get. In number 3, we have this number under the fifth root, so that's equal to that number raised to the power of 1/5. And because percentages behave so much like fractional uncertainties, I can actually just multiply that percentage by 1/5 to get my answer of 2%. In number 4, this is equivalent to 250 plus or minus 0.1 raised to the power of 1/7. So when I multiply that out, this is what I get. And this is my answer for number 4. So that's how you propagate uncertainty when you have a power or a root. This lecture is going to be about propagating uncertainty in physics problems. This is assuming that you already understand all the rules for propagating uncertainty in addition, subtraction, multiplication, division, and powers and roots, and that you understand absolute, fractional, and percent uncertainty. If you're confused about any of those, I've left links to my lectures on each in the description to this video. Physics problems give you values of variables and equations that connect them. Your job is to follow the correct steps to propagate uncertainty to find the uncertainty of the answer. So I'll give you these 4 examples of propagating uncertainty in more complex physics problems where you have to combine the rules that you know to find the answer. These are the rules for propagating uncertainty for addition and subtraction, multiplication and division, and powers and roots. So I'll just apply them as we go through each example. In example 1, the absolute uncertainty of the radius of a 2D plate is delta B. What is the fractional uncertainty of the area of the plate? As usual, the best way to do a physics problem is to just start by writing down everything that you know. I know that the area of a 2D plate is equal to pi r squared, and I know that the absolute uncertainty of r is equal to delta B. That's just a definition that the problem gives me. This means that the fractional uncertainty of r is going to be equal to delta B over B. That's just the way that we express fractional uncertainty as a variable. So I know that the radius has a relative or fractional uncertainty of delta B over B. And that means that the radius squared has a relative uncertainty of 2 times delta B over B, because the rule for raising a number to a power is you multiply the fractional uncertainty by the power to get the new uncertainty. So here the power is 2, so we multiply the fraction by 2. And pi has no uncertainty because it's an exact number, and the rule for multiplying numbers says to add the relative uncertainties of each number. So if I multiply pi times r squared, I'm adding the 0 fractional uncertainty of pi to the 2 delta b over b fractional uncertainty of r squared. So that means the fractional uncertainty of the area of the plate is equal to 2 times delta b over b. That's how you would solve that problem. In number 2, the length of each side of a cube is 3 meters plus or minus 4%. The mass of the cube is 5 kilograms plus or minus 8%. What is the uncertainty of the density of the cube? So again, I'm going to start by writing down everything I know. I know that density is equal to mass divided by volume. And the percent uncertainty of the mass is 8%. And I know that the volume is going to be the length of each side of the cube cubed, raised to the power of 3. So that means the percent uncertainty of the volume is going to be that power times the relative or percent uncertainty. So that's going to be 3 times the percent uncertainty, which means the volume has an uncertainty of 12%. And the rule for dividing two numbers with uncertainties says to add their percent uncertainties together. So the uncertainty of the density will be the percent uncertainty of the mass, which is 8, plus the percent uncertainty of the volume, which is 12, which is equal to 20%. So that's the percent uncertainty of the density. Number 3 says a sphere is inside a cube. Both the diameter of the sphere and the length of any one of the sides of the cube is 20.0 plus or minus 0.8 meters. What is the value of the ratio of the percent uncertainty of the volume of the sphere to the percent uncertainty of the volume of the cube? So I know the volume of the sphere is this, and this is the volume of the cube. I'm calling each side d because that's equal to the length of the diameter as well. I also know that the radius is 1/2 of the diameter, so if I rewrite that volume equation, this is what I get in terms of the diameter. And I know that all these numbers here are exact numbers, so they don't affect the uncertainty, because each one has an uncertainty of 0 and they're being multiplied. And when you multiply numbers with uncertainty, you add their percent uncertainties. So all those numbers to the left are just contributing 0 uncertainty to the final result. So the uncertainty in the sphere is equal to the uncertainty in the diameter cubed, because the other numbers aren't contributing any new uncertainty, which is actually also equal to the uncertainty of the cube, because the cube's equation is just equal to the diameter cubed. So it will have the same uncertainty as the sphere. And if two things are the same, the ratio between them is just 1. So that's the answer to question number 3. These two things have the same uncertainty. You could do a more complicated calculation with the actual numbers that were given, 20 plus or minus 0.8, but the result would be the same. The uncertainty in the sphere would equal the uncertainty in the cube. Problem number 4 says in the equation k equals the square root of a max over x naught, the uncertainty of a max is 20% and the uncertainty of x naught is 12%. What is the uncertainty of k? I'll start by finding the uncertainty in the fraction, and I know that the division rule says to add the relative uncertainties together. So here I'm adding the percent uncertainty of a max to the percent uncertainty of x naught. So that's equal to 32%. So now we need to find the uncertainty of the square root of that answer, and the root rule says to multiply the relative uncertainty by 1 over the root. So this is a square root, so I multiply the percent uncertainty by 1/2, and when I do that I get a final answer of 16%. So if the uncertainty of A max is 20% and the uncertainty of X naught is 12%, the uncertainty of K will definitely be exactly 16% of its value. So that's how you apply those rules together in more complicated problem solving to understand the uncertainty of more complicated values in physics. This is a short video about measurement uncertainty. There's a part of the lab report that asks you to explain your measurement uncertainty, so we're going to talk about what that means here. Measurement uncertainty is the result of imprecision in measuring devices. All measuring devices have some degree of imprecision and therefore some degree of uncertainty. Measurement uncertainty is always the larger of these two choices, either the limit of the instrument, which is half of the smallest increment, multiplied by the number of measurements taken, or a justified estimation of the limit of the measurement procedure as done by the experimenter. So let's see what that looks like in real life. We can imagine that we're measuring a pencil and we're comparing it to a ruler. So we need to use the limit of the instrument, half of the smallest increment, multiplied by the number of measurements taken. I can see that half of the smallest increment here, the smallest increment is 0.5 centimeters. I know this because I can see that there are lines for every centimeter and lines for every half centimeter. So the smallest space between 2 points that this ruler measures is 1/2 of a centimeter. So that's the smallest increment. So I'm going to end up using that in my equation. I now need to know how many measurements are being taken here. This is the part that confuses students a lot because they assume we're just taking one measurement. We're measuring the pencil once. But a measurement doesn't just mean measuring the actual pencil. When we're dealing with measurement uncertainty, a measurement is when we use the instrument and compare the instrument to the object. And when you think about that, we actually have to do that at 2 points on the pencil. We need to see how far it goes this way to the right and how far it goes this way to the left. So we're technically comparing 2 points on the pencil to the instrument. So we're taking 2 measurements here rather than 1. So therefore the uncertainty is going to be that number of measurements times half of the smallest increment, which just turns out to be 0.5 centimeters again. So we would say that the measurement uncertainty of this ruler is 1/2 of a centimeter. And whenever we recorded any values that we measured from this ruler, we would record the values and add an uncertainty of plus or minus 0.5 centimeters to the end. As an example, if I recorded the length of this pencil, I would eyeball it and say it seems to be around 4.3 centimeters centimeters, so I would say that's 4.3 plus or minus 0.5 centimeters. So that's how we would record that based on the measurement uncertainty rules. Readings on a meter like this can also be a little strange. I can see that the smallest increment here is 0.2 volts. V stands for volts here, so 0.2 is the smallest space between two lines. And this is a little counterintuitive, but we would also say that we're taking two measurements here because we're comparing either side of this meter to the background measurements. So that's a little strange, but we would say that we're also taking two measurements in this situation. So for a lot of situations that you deal with, we would say that it's going to be half of the smallest increment times two measurements, which will just become the smallest increment again. So the uncertainty here would be 0.2 volts. So if I were to record this voltage, I can see that that line is around 3.3 or so. I'm not exactly sure. So I would record it as 3.3 plus or minus 0.2 volts. If you're working with a digital reading, the uncertainty will be at least plus or minus one digit of the last significant figure of the reading. As an example, we can imagine we have this digital scale, and right away I can see that the scale goes down to the tenths spot. There's one number after the decimal. So when I put this apple on it, I get a recording of a certain value, 136.4, in this case this is grams. And so the uncertainty here would be plus or minus 0.1 because it's plus or minus one digit of the last significant figure. And here that last significant figure is the 4 after the decimal point. So I would say its mass is 136.4 plus or minus 0.1 grams. So if you're writing a lab report and need to fill out the section explain the measurement uncertainty in the IV or DV, just write about how you followed this method. This video is about how to organize a data table. This is how the data table looks on your lab report. A data table is where you record the data from your experiment before displaying it as a graph. In IB physics, all our data tables will look something like this. We can imagine for this video that the data table that we're making is for a lab where we are investigating how the mass of an object hung from a spring affects the stretch of the spring. So in this case, the independent variable would be mass, and I'm going to say that we're measuring mass in kilograms. So the first thing I would record is the title of my independent variable in the top left corner. So you can see I've recorded mass with parentheses kilograms. The reason why I'm putting the unit up there is so I don't have to write the unit next to each individual measurement that I make in the table below. As long as the unit is on the top, I know what all the units of each measurement are without having to write them over and over again in the table itself. And the dV here would be the stretch of the spring, and that's measured in meters, so I'd write that in the dV section. The plus or minus symbol in the data table stands for the measurement uncertainty of that variable. So I can imagine, for example, that I'm using a scale to measure mass that has an uncertainty of 0.001 kilograms, and I don't need to record that unit a second time because it's already recorded under the IV. And I'm going to imagine that the measurement uncertainty of my dV is also 0.001 meters. That's usually the measurement uncertainty on a meter stick. Above the table is a space to put the control variables. You've probably already written down the control variables in another part of your lab. Here you just have to copy them down a second time so you understand what's not affecting the data. So I'm just going to write down some imagined control variables for this experiment. Okay, I'm now going to make up some data. I'm going to imagine that as you were doing the experiment, you were trying to make sure that your independent variable went up by even increments. So I'm going to imagine that you go up by 0.05 kilograms at a time. So this is what your IVs would look like. So you would fill in your actual data here. This is where you would fill in the measurements that you actually took in your lab report. And in most labs that we do, you're going to take 3 trials of the dV for every IV value that you're measuring. So I'm going to fill those in as well. I'm going to imagine that this is the pattern that shows up. The next step after filling this out is to find the average dV for each row, which is really the average dV for every IV value. And the average dV means the literal mathematical average. And you may remember that the mathematical average is the sum of all your numbers divided by the number of numbers that you're adding. So here you would add up the 3 trials and then divide by 3. So in that first row, you would add 0.012 plus 0.010 plus 0.008, divide by 3, and the answer that you get is 0.010. So that would be your average dV measurement for that IV. Usually we record the unit a second time here. The unit of your average DV is the same as the unit of your regular DV. The next step is to fill out the statistical uncertainty. The statistical uncertainty is uncertainty that you have about your data based on how far apart your measurements are from each other. As an example, if I stepped on a scale 3 times and the first time it said I was 180 pounds and the second time it said I was 181 pounds and then it said I was 179 pounds, I would feel pretty certain about my weight. That range of data would give me a lot of certainty because the numbers are so close to each other. Whereas if I stepped on the scale and it said I was 10 pounds and then I stepped on it again and it said I was 1,000 pounds, that would introduce a lot more uncertainty. So the farther away your numbers are from each other, the farther away your measurements are from each other, the more statistical uncertainty you have. So the formula we use to find that statistical uncertainty is the largest number in your range, that's the largest DV in this case, minus the smallest number in your range divided by 2. So as an example, if the largest number in a range were 6 and the smallest number were 2, 6 minus 2 is equal to 4, and half of that is 2. So we would say that if the largest is 6 and the smallest is 2, the full range is 4 plus or minus 2. So that 2 would be the statistical uncertainty. So we're going to take the largest trial minus the smallest trial divided by 2. This is an example for that first row where the largest is 0.012 and the smallest is 0.008 divided by 2, and this is what we get. So those are the statistical uncertainties, and we usually also record the unit that statistical uncertainty is measured in the box above it. Finally, we need to find the error bar values. The error bar values are something that we'll use when we're actually graphing the data. We'll talk about that more in the Logger Pro video. For now, you just need to know that error bars express uncertainty. So when we're drawing error bars, we want to make sure that we're expressing the full uncertainty that we actually have. And that would be the larger of either the statistical uncertainty or the measurement uncertainty of the DV. So whichever number is larger is the one that I'm going to record in my error bar. So in that first row, I can see that the statistical uncertainty is 0.002 and the measurement uncertainty back in my DV box is 0.001. So statistical uncertainty is bigger. So that's what I would record in my error bar value for the first box. And here the statistical uncertainty is always bigger than or equal to the measurement uncertainty. That's just a coincidence for this lab. So I would record those values specifically. I just compare statistical to measurement and see which one's bigger. Here's an example where the measurement uncertainty is bigger than the statistical uncertainty, and so the error bars would be entirely the measurement uncertainty numbers. It's just whichever one is bigger. The last thing that you need to know about data tables is which part of the table you will take with you to your graph, which parts of this table you will actually graph. So this section and this section is the part that you will not graph. The reason why is that these sections really exist to get you to other sections of your data table. The only reason you take the trials is to get to an average DV measurement. And the only reason you find the statistical uncertainty is to get to your error bar value. So these things are not actually going to graph. The IV always goes on the x-axis of our graph, and the DV always goes on the y-axis, the vertical axis. So these values are what you would put on your x-axis. These values are what you would put on your y-axis. You'll want to also label your x-axis with the name of the independent variable and label your y-axis with the name of the dependent variable. In IB, we do something very specific where we give the name of the variable and then put a dash and then put the unit. So we don't use parentheses for the unit. So if I were writing the x-axis for this graph, I would title it mass dash kilograms like that. And if I were labeling the y-axis, I would call it stretch dash m for meters. So this is what that would look like. When you're creating your graph in Logger Pro, you're going to need to add error bars in both the x direction and the y direction. In the x direction, the error bars will just take the value of the measurement uncertainty. And these are the y-axis error bars. So when you calculate error bars, you're really calculating for the y-axis specifically. And that is everything that you have to know about data tables. In this video, I'm going to show you everything you need to use Logger Pro throughout the entire year. Logger Pro can seem complicated at first, but it's actually a really simple tool, and we'll only be using a few parts of it throughout the whole year, and they'll all be covered in this video. And so if you can understand what's covered in the video, you'll be good for the rest of the course. Logger Pro is designed to create graphs out of sets of data, which will then allow us to create maximum and minimum lines of best fit that are very precise. We want those for our lab reports, so that's what we're going to be using Logger Pro for. Basically, we'll make a graph, put error bars on the graph, and then make a max and min line of best fit. So the first thing I want to know is how to actually make a graph on Logger Pro. When you make a new graph, it automatically comes with an x-axis and a y-axis, and a column right here on the top left for the x and the y numbers. I'm going to fill those in just a second, but before I do, I'm going to show you how to change the names of those axes, because we're not really going to be using x and y as our axes titles for each graph. We're going to be using things like height, position, speed, temperature, things like that, actual things that we're measuring about the world. So we're going to want to change the title of those axes before we actually do anything with them. So to change the title, you can just double click on this square, and that brings up this menu. If you go to column definition right here, this will give you all the important steps to actually naming and titling the column. Just as a heads up, these buttons probably look a little bit different on my computer than they do on yours, just because I'm using a Mac, but they're all in the exact same position in your version of Logger Pro. They just have slightly different symbols than on mine. So let's say that I'm making a position time graph. In a position time graph, time goes on the x-axis, so that's what I'm going to title this. And the short name for this is just the symbol that takes this spot if this name is too long to fit in a position. So the short name for time I can just say is t, and the units of time are seconds or lowercase s. So that's what I would enter in for this column. I'm not really worried about anything else, don't really want it to be any other data type, just keep it as numbers, click done. So now my x-axis has changed to time. Now my y-axis, going to make that position, short name P, units M for meters. And I also want that to be numeric, not a date or anything like that. Okay, so I now have my axes ready and I can start to enter numbers into my table. I'm going to imagine that I did an experiment and tested time equals 1, 2, 3, 4, and 5 seconds. And I'm just going to make up some numbers for the position. Let's say that the position is just increasing similarly. So I'll just do 4, 8, 12, 16, 20. You can see that as soon as I type these numbers, dots appear on my graph. So this is a graph of the data that I just entered in there, if this is the y-axis and this is the x-axis. Now, there are two ways to scale this graph so that the data takes up more space so you can see more of it. You can either drag your mouse down here until it makes this double arrow symbol and drag back and forth. That physically moves where the graph is. If you go to the far right, it turns into the single arrow symbol, that stretches and compresses the graph. That's one way to fit the data to your graph, but there's actually a much simpler way. If you go up here and click this A button in the graph, that auto scales it, so it automatically stretches out the data to take up as much room as possible. So you're always going to want to do this when working with a graph. So that's how you put data on the graph. If you want to change which axis is graphing what, you can go and click on the name of the axis, and it gives you the option of using a different data table. So if I want to use position for the x-axis, I can just go here, click position, and now position is also on my x-axis as well. So I'm going to go back to time for now. So that's how you change what each axis is graphing. Let's imagine that we have error bars for these sets of data. We want to put on a certain amount of error that both the x-axis has and the y-axis has, just because that's going to be pretty common in the experiments. So to make error bars, I'm going to need a separate table to tell the program what values the error will take. What values of the error bar am I taking from my data table? So I'm going to go to Data and click New Manual Column. This is going to add in a new column right here, and the reason why I'm choosing manual and not calculated is that this just means I'm going to enter in the numbers by hand. This is for when you want the computer to calculate the numbers for you, which I'll show you how to use in just a minute. So let's say that I want to calculate the time error, or I want to show the time error bars on this column. So I'll call this time error, and I'll call the short name TE for the error in time. And the units of error are the same as the units for the thing being measured itself, so that's going to be seconds. hit done. And so now I have this new column. And you'll notice this doesn't show up on the graph because I haven't told the graph that one of the axes is the time error. So let's imagine that my measurement uncertainty for time on my data table is 0.4. And that's going to stay the same for all the measurements. So I'm going to enter in manually 0.4 for each part of the column. So if this is my error and I want to represent it as error bars on the graph, what I'm going to do is go back to time, the thing that you want the error bars to be on, go to options, and then click error bar calculations, this checkbox right here. You can either choose a constant, so I could just tell it that all of these points are going to have plus or minus 0.4, and that will actually put the error on my graph for me. If I go back here, I can also just say to use a column. So if I made a column of error like I did right here, I can just select which column I made, time error, and it will use each of these numbers for each of these points. So this is useful if you want some error bars to be bigger than others. If you have one number that has more error, like let's say that this has an error of 2, it will automatically adjust that particular error bar, but not the others. So getting to use a column instead of just a fixed error allows you to change the individual errors on each point. But I'm going to keep all of these at point. I'm going to do the same thing with the y-axis. I'll say new manual column right here. Say position error measured in meters. And I'll just make up some numbers for this. Let's say that we have an error of plus or minus 2, or just plus or minus 1, actually. 2 would be a little big. So I can go back to position because this is the thing that I want to put the error bars on. Double click, go to options, error bar calculations, use column. And so I just made my position error column with all the error values for that. So I can click on that. And now the error bars show up here as well. So this is really good. This is most of what I want to use Logger Pro for. There are just a few more tools that I need to show you. The last step of creating a graph in physics is always putting the maximum and minimum lines of best fit onto the graph so that you can understand the biggest and smallest possible line you can get out of this graph. To do that, you're going to click on this last picture of the lines right here where it says curve fit. You don't want any of the others. Just click curve fit. Now, this gets a little complicated. Just pay close attention. You're going to go to manual, which basically means you're going to get to control the line itself. And make sure you have a linear line selected. You don't want a quadratic line or anything else. If you can't see this line show up in this picture, that might mean that the slope is either too small or too large. You can change the slope of this line right here, and it doesn't really matter what the slope is as long as you can physically see it on your graph so that you can start to manipulate it. For example, if the slope is 0.0001, the line immediately disappears. You can't see it, so you're not going to be able to work with it and drag it along your graph when you hit OK. So you just want to make sure it's something you can see. As long as you can do that, then the M and the B don't actually matter very much. So I'm going to select 1 and 1. And when I do that, this line appears on my graph. I want to be able to drag it around and make a maximum and minimum line of best fit for my graph. To be able to physically move it around the graph, I'm going to go up here, double click on this box, and go to the bottom right here where it says Enable Line Drag. When I click on that, these diamonds appear on either side of the line, so now I can physically drag it along my graph. These two control the slope, and this middle one right here controls the up-down position of the line. So let's say that you want a maximum line of best fit. To make a maximum line of best fit, you want it in the bottom right corner of the square of uncertainty down here, so that's about right here. And in the top, you want it in the top left. That'll make it as steep as possible. If I want to make this a little more clear, I can also drag this graph down a little bit so I can see where this is a little bit better. I would say that that's my maximum line of best fit. That is the steepest line that I can get that goes through all of these error regions. If I made it any steeper, it would no longer go through some of these boxes. Like if it were up here, it would no longer be going through this one, so it's not actually a possible line for my graph. You'll notice that this gives you the slope and the y-intercept of this line. So when your lab reports ask you for what is the slope and y-intercept of the maximum line of best fit, this box right here is where you're going to get that from. My slope is 5.275 and my y-intercept is negative 3.969. So that's where you get the numbers from for your maximum and minimum line of best fit equations. So this is my maximum line of best fit. So now I'm just going to add another line in the same way, go to manual and make my minimum line of best fit. So it's still linear. I can still see the line, so I don't need to adjust the slope at all. I hit OK, go over here, enable line drag, and now I can move this around like this. Okay, so I would say that this is my minimum line of best fit. So that's basically like 95% of what you need to know about Logger Pro right there. There's just a little bit more information you're going to need to know just to do something very specific with Logger Pro, which is linearization. If you don't know what linearization is yet, that's totally okay. I just need to show you basically one more small tool that you can use to figure out some more information. And that's going to be making a new calculated column right here. This is the very last thing that you need to know about Logger Pro. Let's say that we're doing something specific to our time measurements to change the shape of the graph. Let's say, for example, that we want to square our time values, but we don't want to do that by hand. We can just have the computer do that for us to avoid having to do calculations. So if instead of graphing position versus time, I want to graph position versus time squared, I can go to Data, New Calculated Column. I'm going to name this new column Time Squared. And the short name will be T squared. And if we're squaring time, the units of that are going to be seconds squared. So to carry out a formula on a set of data, you just need to go to Variables, select the column that you would like to perform the function on, and then write out what you want to do to that function. So in this case, I want to square time. So I hit Done. And now I have a new column of all the time values squared. My original time values were 1, 2, 3, 4, 5, and so my new time squared values are 1, 4, 9, 16, and 25. If I want to graph this, I can just go down here and tell the machine to graph time squared instead of time. Obviously, this makes my graph look pretty weird, but this is what it would come out to if I graphed time squared instead of time. Obviously, if I wanted to put a new error on these lines, I could just make a new column, time squared error. I'll just make up numbers for right now. I can just go over here, error bar calculations, use column, time squared error. And so I could add error bars there as well. So if you want to make a new calculated column of numbers, you just go here, select new calculated column, and then just write out the equation that you want to perform on your variables. And that's it. That's literally everything that you're going to need to know about Logger Pro for this entire course. So as long as you can just stick to those functions, you'll be good. Now that you're done making your graph on Logger Pro, the next step of your lab report is to find the average line of best fit from your max and min lines of best fit. So a line of best fit is a straight line that best represents the data on a scatter plot. The line does not have to pass through every point to best represent the pattern of the data. So you can see that even though this line that's drawn on this data is not actually physically passing through every point, it still does a pretty good job of predicting where that data is going to appear. So that's the goal for a line of best fit. The goal for a lab report in general is to predict what will happen in the future, or predict what will happen for quantities that you haven't tested yet. And the way that you can do that is by using a mathematical line like this to find what the value of that line will be for quantities that you haven't tested. This is another example of a line of best fit. One thing to say before we start, if you're drawing your physical graph on your lab report, do not connect the dots on your graph. This is completely meaningless and gives us no useful information at all. So please don't do that as you're drawing this. So by now you've added error bars onto your Logger Pro graph, and those error bars create areas of uncertainty where your data could possibly be. And you've drawn a maximum line of best fit through those areas of uncertainty, and you've drawn a minimum line of best fit as well, lines that have the largest possible slope and the smallest possible slope that can still fit through most of those areas. So our idea is that if that's the biggest possible line you can get out of this data and the smallest possible line you can get out of this data, the most reasonable estimate for what your data is actually doing, the line that your data is actually on, would be something right in between the minimum line and the maximum line. So if we can find the average of those two lines, then we'll have the best estimate that we can get of what your data is actually doing. So now we just need to understand how to actually take the average of two lines. So the first step in taking the average of two lines is to write the equation for both lines. There's a space on your lab report that looks like this. This is where you're going to physically copy down the equation for each line. And to get the equation for each line, you're going to need to use LoggerPro. These four spaces specifically are where you're going to fill in the information that you get from LoggerPro. Everything else you can fill in from previous parts of your lab report, but these four spaces you're going to need to use the equations that you got for that maximum and minimum best line, for that maximum and minimum best fit line. So the boxes for the manual fit lines that give you the slope and y-intercept for the max and min lines look something like this on LoggerPro. So you're going to take the slope of your maximum line and the y-intercept of your maximum line and put them here and here, and the slope of the minimum line and the y-intercept of the minimum line and put them here and here. You'll notice that most of the time the y-intercept of the minimum line is actually going to be larger than that of the maximum line. This makes sense if you think about it as having the smallest possible slope. So I'm going to copy down these numbers here. And you don't have to copy down every single number that LoggerPro gives you. Round to a reasonable number of significant figures based on your original measurements. Okay, this is everything that you have to fill in. The y variable is just another name for the name of the dependent variable. The units are the units that dv is measured in. The slope unit is going to be the dv unit over the iv unit, just because slope is rise over run. And on a graph like this, we're measuring the dv on the y-axis and the iv on the x-axis. So the slope units will be the units of dv over the units of iv. The x variable is the independent variable, so you'll just copy down the name of that variable, and the x unit is just going to be the unit of IV. And finally, the y-intercept units are also going to be the dv units, the dependent variable units, because if you think about it, the y-intercept is going to be measured using the units of the y-axis. So I'm going to imagine that we're comparing displacement and time. So displacement measured in meters is our dependent variable, and time measured in seconds is our independent variable. So those would go where they go. You can see that the slope units are the unit of the dv over the unit of the iv. So here that would be meters in the numerator and seconds in the denominator. So that's how we would fill out the equation for the maximum and minimum curves of best fit. Okay, the next section of the lab report asks you to find the average of the slope and the y-intercept and the absolute uncertainty of the slope and y-intercept, and sometimes it will also ask you for the percent uncertainty of one or the other. These are the equations that you need to use for each one. These equations are also given to you on the left in those boxes. You can see as an example below average value, it shows sum over the number of values. That's the equation for the average of numbers. I'm just giving them to you like this, so it's a little more clear what you have to do. So you can see that as an example, to find the average slope, you add the slope of the maximum line plus the slope of the minimum line divided by 2. So it's literally the mathematical average of the two slopes from your experiment. And the absolute uncertainty is going to be the largest slope minus the smallest slope divided by 2. Based on how we've been using uncertainty in previous parts of the class, that makes sense. It's just half of the range of the possible values that that slope could take. If I take that max and min line of best fit equation that I got in the previous slides and plug in the slopes and the y-intercepts to their correct spots, these are the numbers that I would get for each value. Finally, the percent uncertainty of the slope is just the absolute uncertainty divided by the average slope times 100. So I'm just going to take those numbers and multiply them by 100%, and that will be my slope uncertainty. So here it's 22% uncertain. The next step is to get the average best fit equation itself. And this is kind of one of the big central goals of the lab report. If you can get an equation that tells you what value your dv is going to take for any iv, you've found a way of basically predicting anything that will happen in your experiment, which is a pretty big accomplishment. The goal of all science is to predict things. The goal of physics specifically is to predict motion. And so if you have an equation that can make a prediction for any independent variable and tell you what the dependent variable will be, that's a huge accomplishment. So let's see how we fill in this average curve of best fit equation. This is what you're going to put into each section. The y variable is the dependent variable. The y units are the dv units. The slope of this average line of best fit is going to be the average slope that you calculated in that previous section. The slope uncertainty is going to be equal to the absolute uncertainty of the slope. The slope units are the dv unit over the iv unit. The x variable is the independent variable. The x units are the units of the independent variable. The y-intercept is going to be that average y-intercept that you calculated. And you're also going to include the y-intercept uncertainty and the y-intercept units. So here, these are the units that I used in my experiment, and these are the numbers that I got from the previous section. So this would be my average curve of best fit equation. This equation is telling me that if I plug in any time, I can multiply it by 3.2 plus or minus 0.7 meters per second, add negative 0.7 plus or minus 4.3 meters, and that's going to give me a specific displacement as a result. And so that's how you create the average line of best fit from the maximum and minimum lines of best fit that you get from Logger Pro. This video is about the idea of vectors versus scalars. So vectors and scalars are both quantities. They're both amounts of something. The difference between them is that vectors have magnitude or size and direction, whereas scalars are quantities that have size but no direction. So some examples of vectors could be displacement, force, because if you put a force on an object, you have to push it in a certain direction with a certain size, velocity, acceleration, and momentum. And some examples of scalars could be things like length, area, temperature, mass, and energy. Just as an example, with temperature can have a certain magnitude, a certain size, but you can't really point with your finger and say it's 70 degrees Fahrenheit that way, as an example. So because temperature can't have a direction, we would say it's a scalar rather than a vector. So as an example, vectors have both a size and direction. So if you're pushing on something, as an example, it's not really possible to push on something without having both a size and a direction to that push. And the direction that you're pushing something matters. For example, we just saw two people pushing something in the same direction, whereas if somebody pushes this way, it's going to go off in a different direction as a result. So the directions of vectors are going to matter a lot in how they relate to each other. Scalars, on the other hand, do not have a direction, so things like temperature can get bigger or smaller, but they can't point up or down or left or right or forward and backward. They can just increase or decrease in magnitude. So this is everything you have to know. Vectors are anything that have a magnitude and direction, and scalars are anything that do not have direction. They only have magnitude. They only have size in the measurement. This video is about labeling and adding vectors. Vectors are quantities that have both magnitude, which is just another word for size, and direction. To show their magnitude and direction, we draw vectors as arrows, because arrows also can have a size and a direction. To draw a vector, just draw an arrow pointing in the vector's direction and then write the magnitude of the vector above it. So as an example, if I want to draw a vector, I need to give it a direction and a magnitude. So I'm going to give that arrow a certain size and then label its magnitude above the arrow like this. So this vector literally means 10 meters to the right. These are a few more examples of vectors with specific labels. The arrow's length depends on the magnitude. The bigger the magnitude, the bigger the arrow. And if you double the size of the magnitude, you double the size of the vector as well. So if this is 10 meters and we want to draw a 20 meter vector, we need to draw an arrow that's exactly twice as big as that original arrow. The reason why we proportion them this way is that this helps us see the relationship between multiple vectors. Just as an example, if you're trying to describe motion like distance or displacement using a vector, having the sizes of the arrows representing the actual sizes of the arrows can help you visualize motion much more easily than if they were just arbitrary sizes like that. So you get a clearer idea of what's going on. The symbol we use for labeling vectors is a letter with an arrow above it. So that's a variable, that's a stand-in for a vector. So this is vector A. Vector A is equal to 10 meters to the right. And it's totally arbitrary which letter we use for which vector, as long as we're using a letter with an arrow above it. That's a variable that stands in for a vector. The same letter without an arrow above it means the scalar magnitude of that vector. So if I just drew E without an arrow above it and E with an arrow above it means 10 meters to the right, E by itself just means 10 meters. So that's a notation that we use. So I can see these are all vector quantities, and if I wanted to represent them as scalars, this is how I would do that. Pretty straightforward. If you multiply a positive scalar by a vector, multiply the scalar by the magnitude of the vector and keep the direction the same. So as an example, if I multiply this by 2, that means I'm multiplying the magnitude by 2, but I'm keeping the direction the same. So 2 times vector A is equal to 20 meters because it's 2 times the magnitude, and the direction is the same, but the vector is now twice as long. If I multiplied the vector by 1/2, this is what it would look like. Pretty straightforward. If you multiply a negative scalar by a vector, multiply the scalar by the magnitude of the vector and flip the vector to face in the opposite direction. So multiplying by a negative number flips the direction of the vector to aim in the opposite direction. So negative 2 times A would be 20 meters to the left here. Now we're in the part of the video about adding vectors. There are rules that make adding vectors different than adding regular numbers because vectors also include direction. So the directions of the vectors you're adding are going to matter for their sum. So the first step to adding vectors is to connect the tip of one vector to the tail of the other. The tip of the vector is the point of the vector right here, the very front of the arrow. And the tail of the vector is the opposite end of the vector right here. So just remember the point is the tip and the opposite end is the tail. So we're going to connect the tip of one vector to the tail of the other, and it does not matter which order we do this in. I'll talk about that more later, but what matters is that the tip of one is connected to the tail of the other. So if you watch up here, you can see these two ways of connecting the tip and tail are correct, and these two are incorrect. The connections on the right are incorrect and not how you use the tip to tail method. So step number 2 is to draw a vector that begins with a tail at the tail of the first vector and ends with a tip at the tip of the second vector or the last vector that you're adding. So if I draw that for these two vectors, the 4 and the 3, I get a new vector that looks like this. So it starts at the tail of the first and ends at the tip of the last like that. So an incorrect way of doing this would be to draw it like this. For some reason, a lot of students do this their first time adding vectors, so please make sure that you're drawing from the tail of the first to the tip of the last. This one's going in the wrong direction. Step number 3 is to find the magnitude of the new vector using the magnitudes of the original vectors and geometry. In this case here specifically, I can see that these vectors are forming a right triangle. And I remember from math class that if I'm missing the side of a right triangle, I can use the Pythagorean theorem, a squared plus b squared equals c squared. So plugging in my numbers here gets me a final vector value of 5. We're going to be using the Pythagorean theorem a lot in this class because vectors that form right triangles come up a lot. We'll learn how to deal with more complicated shapes later. The main thing I want you to know for now is that you'll have to use geometry to figure out the length of the missing vector in addition to the other two steps. So this is it. This is the answer. What this is saying is that the two vectors added together, their sum is equal to this new vector of 5 pointing in that very specific direction. The direction of the sum matters a lot. So when you're adding two vectors together, you have to consider both their size and their direction and use this 3-step process to find what that final vector looks like. Just to give you an intuition of why these vectors look the way that they do, why they add together in this way, we can imagine that you're running along a soccer field. And let's imagine to start off that you run at a certain speed along the field, from one end of the field to the other. And then you run at a new speed across the field from one side of the field to the other like this. If someone were to tell you to run in both of those directions at the same time, to perform both of those motions at once, that would be like adding those two vectors together, adding those two motions together that you were performing. And if you add both of those vectors together, this is what it looks like. And so you can see that by adding those two vectors together, we get this new resultant vector, the blue vector, that's not just the numerical sum of the two. It's not just the regular old sum of the two. We have to use this tip to tail method to find that final value. So that's why we say that the sum is what it is for vectors. If we have two vectors pointing in the same direction, it's very easy. We just do the tip to tail method again, connect tip to tail, draw that new connecting vector from the beginning of the first to the end of the last, and using geometry, it's pretty obvious that this has a length of 11. If we have vectors pointing in opposite directions, again, we connect the tip of one to the tail of the other like this, so that 2 is kind of pushing back into the 6. And when I draw that new final vector from the tail of the first to the tip of the last, I can see that this is what it looks like, and so it's basically going to have a length of 6 minus 2, which is equal to 4. So that's how you'd find the size of vectors that are pointing along the same line. The order that we add regular numbers doesn't matter, and mathematicians have a word for this. They call this the commutative property. So no matter which order we add multiple numbers, it's always going to come out to be the same resultant number. In the same way, vectors actually also have the commutative property. The order that we add vectors does not matter. Any order will get the same result. So if I add these tip to tail, it doesn't matter if I do it like this or like this. Both ways, as long as they are tip to tail, yield the same final vector. We're going to do a quick check for understanding. You might want to pause the video here and just see if you can determine the size of each vector sum. I'm going to come back in just a minute and give you the answer. Okay, let's go through. Connecting these first two tip to tail, I can see that 12 and 20 are just working together, so that overall vector is going to be 32 to the right. Connecting the second two tip to tail, this time they're working against each other, and so that new final connecting vector is going to be 4 pointing up. This next set here, I'm going to connect tip to tail again, and I can see that when I draw that final vector from the tail of the first to the tip of the last, it's forming a right triangle. So if I use the Pythagorean theorem, I find this is equal to 22.36 pointing down like that. Finally, I have these two down here, and so if I connect them tip to tail, I find that it looks like this. 7.07 after I use the Pythagorean theorem. And that's what you have to know about adding and labeling vectors. This video is about recording the angle of a vector. We usually record the angle of a vector between 0 and 90 degrees, but we have a full 360 degrees that the vector can exist in. So we need a way of labeling where it is in that circle. So I'm going to show you a way that we do that. This vector is pointing perfectly east. I've just come up with this compass rose to help our direction. So I can see right now that the vector is moving north from east. I'm tilting it up so that it moves north from east until it's at an angle of 30 degrees. So the name that we would give that angle is specifically 30 degrees north of east. You had to start off at east and then go north by 30 degrees, or angle yourself north by 30 degrees to get to that angle. So I could label that angle 30 degrees north of east. If I had a vector that started north and went down 30 degrees toward the east like this angle would be 30 degrees east of north, if that makes sense. You started off at north and went 30 degrees east of north. So those two vectors are different. The angles are different from each other. So if we say 30 degrees north of east, that means something different than 30 degrees east of north. You can pause the video for a minute and see if you can describe these vectors using that same notation. I'll come back in just a second to give you the answers. Okay, here they are. You might have noticed that we can actually describe the angle of any vector in both ways, because we know that, for example, 75 degrees east of north, if you go 15 degrees further, you're going to hit the eastern mark, so that means it's also 15 degrees north of east. So if you want to flip the order of the words, you can actually just subtract your angle from 90, and the result will be the other angle when you have the words flipped. So 28 degrees north of west, if we subtract 28 from 90, we get 62. So 28 degrees north of west is equal to 62 degrees west of north. It's a convention in physics to almost always draw the angle of a vector between the vector and an imagined horizontal line. In other words, we usually record vector angles in these directions: north of east, north of west, south of west, and we rarely use other directions. So what I'm saying is that we imagine that there's a horizontal line at the base of the vector like this, and the angle is recorded between that horizontal line and the base of the vector. We very rarely use vertical lines. We will sometimes, but it's more rare. The convention, just to make it a little easier, is to always use the horizontal. So vector angles will normally be recorded like you see on the left rather than on the right, but the right is still definitely fair game. We can still record angles that way, so we'll have to show you how to deal with that later. Okay, this video is about finding the angle of a vector. After adding two vectors that point up, down, left, or right together, you need to find the angle. Vectors communicate magnitude and direction, so the direction of the sum of vectors matters a lot for our math and for what we're trying to accomplish. Right now we're just adding simple vectors that point up, down, left, and right, and they form right triangles with their resultants. So we can use trig to find the angles of the vectors, because trigonometry helps us understand angles and their relationship to right triangles. So I'll show you an example of using trig on this first sum. I can see I have 10 to the right, 5 down, so I combine them tip to tail like this, draw that new connecting vector, and using the Pythagorean theorem, I see that it's 11.2. And I remember the convention for vectors is to try to find the angle between the vector and the horizontal line like this. So I'm trying to find that angle. And I remember there's a trig identity that says that if I'm trying to find the angle and I have the sides, I can plug the sides into this identity to find the angle. And that's an inverse trig function. Because I have all three sides, I can choose any inverse trig function I want. I'm going to go with tan inverse, which is opposite over adjacent. And I can see my opposite side here is 5, my adjacent is 10, so I plug that in, and if I put that into my calculator, I get 26.6 degrees. So that would be the angle of the vector, the sum of those two smaller vectors. So 10 to the right plus 5 down is equal to 11.2 at an angle of 26.6 degrees south of east. I can do the same thing with the 4 and the 6, so I combine them tip to tail, draw that new connecting vector. Pythagorean theorem tells me it's 7.2. I want to find the angle between the base and the horizontal like this, so plugging into my trig identity again, the opposite side is 6 and the adjacent is 4, so I get an angle of 56.3 degrees north of west when I plug that into my calculator. These are 4 example problems that you can try if you'd like to pause the video. You can see here that I'm only giving you 2 out of 3 of the sides of each triangle. So to find the angle of the vector, you're going to have to decide which trig identity to use. So sine connects opposite and hypotenuse, cosine connects adjacent and hypotenuse, and tan connects opposite and adjacent. These are the answers when you plug them in. So if any of that didn't make sense to you, please feel free to pause the video and ask me about it in class. Here's a real-world example of using vector angles to solve problems. You start swimming straight across a river at 3 meters per second, but the river's current pulls you downstream at 5 meters per second. What velocity do you have in total, and what direction do you move in? So you're trying to swim across the river at 3 meters per second, but the current is working with you, or it's pushing you 5 meters per second downstream like this. So we need to know what velocity do we have in total in the river and what direction do we move in. That's just code for what angle are you moving in the river. So adding these two vectors together, I can use the tip to tail method, connect that new total vector, and I get 5.8 meters per second using the Pythagorean theorem. And when I solve for this angle, I get 59 degrees. So what this is saying is that if you're in a river and you're swimming at 3 meters per second straight across the river, but the river is pushing you 5 meters per second down the river, your actual true velocity will be 5.8 meters per second at an angle of 59 degrees from the real path that you want to take straight across the river. So that's how you use trig to find the angles of vectors. This video is about x and y components of vectors. All vectors have what's called an x component and a y component. So this is vector A. I'm going to be using this as an example. The x component is how far in the horizontal direction the vector travels. So if this is vector A, this is its x component right here. And its y component is how far in the vertical direction the vector travels. So that would be the y component of vector A. That's how far in the up-down direction it goes. So we call these x and y components because they go along the x and y axis of a graph. So we can have x components and we can have y components. And that really just means that they're pointing along the x or y axis. X and y components are themselves vectors. They also have directions. Like vector A is going up and to the right, so its x component points to the right and its y component points up. And we have this special label for vectors that are x and y components of other vectors. If the original vector is A, the x component of A will be ax and the y component will be ay. So we could draw these like this. Just as a real world example, we could imagine a bird flying up in a certain direction, and the vector of the bird's motion, I'm going to call vector A. The x component of the bird's motion, ax, could be thought of as how far along the ground the bird's shadow traveled as it moved. And the y component of the bird's motion would be how high into the air the bird went. So x and y components can have real physical meanings in addition to the original vector that they're making up. Even if you have a perfectly horizontal or perfectly vertical vector, we can still say that it technically has an x and y component. The x component is how far it goes in the horizontal direction, and so if this is 5 meters perfectly horizontally, that means the x component is just 5 meters. It's the same as the original vector. And we would just say that the y component is 0 here because it's not going up or down at all. So this would be like the bird moving 5 meters along the ground. If we were to ask for its x component, we would be really asking for how far its shadow moved along the ground, which we know would be 5 meters. And if we asked for its y component, we'd really be asking how high into the air did it go, and we know that that would be 0 meters. There are two general rules for x and y components and how they relate to a vector. You can see, first of all, that they actually obey the rules of vector addition, the tip-to-tail method, and the x component plus the y component as vectors, if we're adding them using vector math rather than regular math, the tip-to-tail method means that the x and y components always add together to be the original vector. So a vector is equal to the sum of its x and y components. So that's the first rule. You'll also notice that no matter how we draw the x component and no matter how we draw the y component, they're always going to form a right triangle with the original vector. So as another example, if we have this vector here and this is its x component and this is its y component, we can see that when we put them together in vector addition, they're equal to the original vector. So that will always be true. One common mistake with this rule is that students sometimes assume that the numbers themselves add up to be the total of the vector. So if we imagine that the x component is 3 and the y is 4, that overall vector using the Pythagorean theorem will be 5. It won't be 7. So it's not that the scalars add together, it's that the vectors using vector addition add together to make that total vector. So I can see here that the scalar quantities look like this, which means that this rule does not work for scalars. It only works when you're using the full vector and the tip-to-tail method to find the answer. So just adding the scalars together won't work. You may have noticed, however, that no matter how we draw vectors, their x and y components always form perfect right triangles with them when we draw them, because the x and y components are by definition at 90-degree angles to each other. So because of the Pythagorean theorem, that means that the x and y components will always be related to the full vector using the Pythagorean theorem, a squared plus b squared equals c squared. So this will always be true. And if I rearrange this into a general rule, the total vector is going to be equal to the square root of the squares of its own x and y component if I draw it as a scalar rather than a vector like this. So if we just focus on the scalar quantities, this will always be true for the x and y components of a vector. This is just a summary of what we've talked about, and that's what you need to know about x and y components. This is a review of trigonometry. This part is covering what the trig identities mean and finding the angle of a triangle. So trig identities are fractions of different side lengths of a right triangle. That's literally all that they are. They're just the fraction values of different sides of a right triangle. We label the sides based on which angle of the right triangle we're looking at. We call the sides opposite for the farthest side from the angle, adjacent for the side next to the angle, and hypotenuse for the hypotenuse of the triangle. So on this right triangle here, this would be the opposite side. It's the farthest from the angle. This is the adjacent side. It's adjacent next to the angle, and it's not the hypotenuse. And this is the longest side, so this would be the hypotenuse. If I were to move the angle to this side, I can see that the opposite side is now on the bottom here, and the adjacent side is now up there. So those two sides switched, but the hypotenuse stayed the same. So the opposite and adjacent depend on which angle you're looking at in the triangle. The trig functions appear here on your calculator. You can see that sine, cosine, and tangent are all right here. Make sure that before you do math in this class, you've pressed mode on your calculator. And when you open up mode, you've set the setting for angles to degrees rather than radians. We don't work with radians in this class. We'll always be using degrees. So if you're getting strange results for your numbers, just click mode and make sure that you've pressed degrees rather than radians. So these are what the three trig identities mean. Sine of an angle is just the opposite side divided by the hypotenuse. Cosine is the adjacent divided by the hypotenuse, and tangent is the opposite over the adjacent. So as an example, I'm going to make up some numbers and say this triangle has one side that's 3, one side that's 4, and one side that's 5, like this. That actually fits the Pythagorean theorem. So I'm going to find the value of all three trig identities, sine, cosine, and tangent. And to do that, the first thing I need to do is identify which side is opposite, which side is adjacent, and which side is the hypotenuse. And I can see that the opposite side is the side farthest from the angle, so that will be the 3. I'm going to call that blue. The adjacent side is the side next to the angle that's not the hypotenuse, so that's 4. And the hypotenuse is 5. So now that I've identified these, I can just plug them into my trig identities and see what those values are. So sine is 3 over 5, opposite over hypotenuse. Cosine is 4 over 5, and tangent is 3 over 4. So these are their literal values for that triangle. So again, all that trig identities are the ratios of two sides of a right triangle, nothing else. I can now compare the trig identities for the second angle up here. I'm going to call this the green angle instead. And I can see that for this green angle, the 3 is now the adjacent side, the 4 is the opposite side, and the 5 is the hypotenuse. So plugging this in, these are the trig identities for that other second angle of the triangle. This video is a review of trigonometry, which is about finding a side of a triangle given the angle and another side of the triangle. We can use sine, cosine, and tangent to find missing sides of a triangle given another side and the angle of the triangle. I'm not going to run through these 3 steps. You can read them on your own. I'm just going to give you a few examples of using them. Just as a reminder, your trig identities appear here on your calculator, sine, cosine, and tangent. And before you use these, please make sure to hit mode and make sure that your calculator is set to degrees rather than radians. That's a very common mistake. Okay, so let's look at this first example. So I've got a triangle with a hypotenuse of 10 and an angle of 30 degrees, and I'm trying to find that missing side on the right. So I'm going to go through these steps. Step number 1, determine which trig identity to use. To do this, determine which side of the triangle you know and which side you're trying to find. The trig identity that has both is the one you want to use. So here I can see that I have the hypotenuse and we need the opposite side. The 10 is the hypotenuse and the thing we're trying to find is the opposite side. And the only identity that connects opposite and hypotenuse is sine, so we'll use sine. The second step is to rearrange the trig identity so that the side you're trying to find is on one side of the equation and everything else is on the other side. So here I'm trying to find the opposite side of the triangle. So if I rearrange this equation so that opposite is by itself on one side, I'm going to start by multiplying both sides by hypotenuse. Those go away. And I get that the opposite side is equal to the hypotenuse times sine of the angle. The last step is to plug in the values you know into your identity and solve. So when I plug this in, 10 times sine of 30 degrees is equal to the opposite side. And when I plug this into my calculator, I get the opposite side is equal to 10 times 0.5, which is equal to 5. So that's how you find the missing side of a right triangle using trigonometry. So this would be 5. Example number 2, I'm going to follow those same steps. Here I have the hypotenuse and the adjacent side. So the only thing that connects hypotenuse and adjacent is cosine, so that's what I'm going to use. And because I'm trying to find the adjacent side, I need to rearrange that equation to get adjacent by itself. This is what that looks like. And finally, plugging in my numbers, 10 times cosine of 30, according to my calculator, is 8.7. So that will be the length of the opposite side of the triangle. Example number 3, you can see this time we're trying to find the hypotenuse and we have the opposite side. The only thing that connects those is sine, so that's what we'll use. And now I have to rearrange that for the hypotenuse to get the hypotenuse by itself. And this is what that looks like. The hypotenuse is equal to the opposite side over sine theta. Finally, I'm just plugging in my values. The hypotenuse is equal to 8 over sine of 60, and according to my calculator, that's 9.2, so that's the value of the hypotenuse. Example 4, I have the opposite side and I'm trying to find the adjacent side, and the only identity that connects those is tangent. So using tangent, I'm trying to solve for the adjacent side, so I'm going to rearrange this to get the adjacent side by itself. This is what I get. Plugging in my numbers gets me an adjacent side of 4.7, so that's my answer there. Example number 5, I'm trying to find the hypotenuse using the adjacent side. So cosine connects those. Rearranging cosine to get the hypotenuse looks like this. And plugging in my numbers looks like this. So the hypotenuse is 51.5. Example number 6, I have the adjacent side and I'm looking for the opposite. Tangent connects those two. Plugging in my numbers and solving for the opposite side gets me this. And plugging in my specific numbers gets me an opposite side of 13.5. So that's how you use trig to find the missing sides of a right triangle. In this review of trigonometry, we're going to be talking about inverse trig functions. First of all, we need to define what it means to be an inverse function in general. If a function takes in a specific x and gives you y, an inverse function takes in that y and gives you x. So that notation I've written is what that looks like. As an example, y is equal to 5x plus 2 has an inverse function of y is equal to x minus 2 divided by 5. You can see based on the table that I made that if you put any number into x and get y, in the inverse function, if you put that y value back into x, you're going to get the original x value back in y. So as an example, if you put x is equal to 2 into y equals 5x plus 2, you're going to get y equals 12 as a result. And if you take 12 and put that into x in y equals x minus 2 over 5, you're going to get y is equal to 2, the original x value that you plugged in. So an inverse function kind of reverses the x and the y like that. Similarly, a regular trig function takes in an angle and gives you the ratio of two sides of the triangle. An inverse trig function takes in the ratio of two sides of a triangle and gives you an angle, so it works just like any other inverse function. Using the inverse trig functions is going to require your calculator. There's no way in the type of trig we're doing to do this in your head. So on your calculator, to find the inverse trig functions, you're going to see them down here. They're labeled with a -1 next to them in blue. So you can see there's sine inverse, cosine inverse, and tangent inverse in blue there. To get the blue functions, you'll just have to press second right here. And then if you press sine, cosine, or tangent, that will make it sine inverse, cosine inverse, and tangent inverse instead, as long as you press that second function button. And as usual, just make sure you've pressed mode and make sure that your answers are in degrees and not in radians. Here's an example of using an inverse trig function to find an angle. Here I have a right triangle with a hypotenuse of 10 and an opposite side of 8, and I want to know that angle, the value of that angle. So I need an inverse trig function because I'm trying to find an angle. In general, if I'm looking for an angle, I'll use an inverse trig function. If I'm looking for a side, I'll use a regular trig function. Because I'm looking for the angle and I have the opposite and the hypotenuse, I'm going to use sine inverse because sine connects opposite and hypotenuse. Plugging in my specific numbers gets me 8 over 10. So if I plug sine inverse of 8 over 10 into my calculator, I get the answer of 53.1 degrees. So that would be the angle for that triangle. For example number 2, I have a hypotenuse of 24 and an adjacent side of 11. And because I have the hypotenuse and the adjacent, I'm going to use cosine. And because I'm looking for an angle, I'm using an inverse function. So I'm using inverse cosine. Plugging in my numbers gets me 62.7 degrees when I put that into my calculator. Example number 3, I have the opposite side and the adjacent side. So that means I'll be using tangent. And because I'm looking for the angle, I'll be using an inverse trig function. Plugging this in, I get 54.5 degrees. Here's another example. This time the angle is on the opposite side. So I can see that because that angle is up there, 8 is the opposite side of the triangle and 20 is the hypotenuse. So I'm using sine. And I get 23.6 degrees. Here's another example. This time 3 is adjacent and 12 is the hypotenuse. So I'm using cosine. And I get 75.5 degrees. Example number 6, I've got an opposite and an adjacent, so I'm using tangent, and it's tangent inverse because I'm trying to find the angle. Plugging this in gets me 56.3 degrees. So that's how you use inverse trig functions to find the angle of a triangle. This video is about finding x and y components using trig. All x and y components form right triangles with the vectors of which they are components, so we can find their values using trig. I'm going to give you an example. So each of these vectors has an x and y component. I'm going to draw what those are. This is the x component for each, and this is the y component for each, just how far they go along the x-axis and how far they go along the y-axis. So So if you don't remember how to solve for missing sides of a right triangle using trig, I've left a separate video explaining how to do that in the description of this video, but if you do remember, I'm just going to go on ahead and begin to do that. So I can see the adjacent side here will be equal to the hypotenuse times the cosine of the angle. Plugging in the specific numbers that I have allows me to solve for the adjacent side of each right triangle. So those are the values of the x components. And I can see that the y component is the opposite side of each triangle, so solving for the opposite side gets me these values for each triangle here. So that's how you would solve for the y component of that vector, and in general, that's how we'll use trig to find the x and y components of any vector that we have, just using the angle and the magnitude. There will definitely be times when the angle is drawn with the vertical instead of the horizontal, but we can still find the x and y component. So just drawing those x and y components, I'm just making sure here as I draw them that the angle is still inside of that right triangle. If it's inside of the right triangle, it will be much easier for me to use trig. So here I can see that the adjacent sides are actually going to be the y components. So plugging in what I have here allows me to solve for the y components of each vector. And plugging in what I have for the opposite side, which I can see here is the x component, allows me to solve for the x components like this. And that's how you solve for the x and y components of vectors using the angle of the vector. This is going to be a short video on how to add complex vectors together. What I mean by complex vectors is vectors that do not just follow a perfectly horizontal or vertical shape. They can have an angle like this, and we haven't really added those together in class yet. All the vectors that we've added so far have just pointed up, down, left, or right. So you need to have a method of adding these together as well. As you can see, I've already connected them tip to tail like this, and I need to find the resultant vector that looks like this. The problem is I don't have a clear way of doing that right now. So I'm going to show you the method that we use for finding that resultant vector of two smaller vectors that have angles to them. So the first step is going to be to find the x and y components of each individual vector. And you'll notice when I do that, that the total x component of the two vectors working together and the total y component of the two vectors working together actually makes the total x component and the total y component of that overall vector, as you can see from my picture. So when I add those red arrows together, they make the total x component of the resultant vector. And when I add the blue arrows together, they make the total y component of the resultant vector. This is going to be a rule for adding all vectors together. The sum of the x components is equal to the x component of the resultant vector, and the sum of the y components is equal to the y component of the resultant vector. So we're just going to add those together to find the resultant. And the resultant itself, because you have its x component and its y component, using the Pythagorean theorem, you can prove that the resultant itself will be equal to the square root of its own x component squared plus its own y component squared. And because the x and y components are equal to the sums of all the individual x and y components, I can rewrite the formula like this. To find the angle, you're just going to take tan inverse of the sum of the y components over the sum of the x components, because as you can see, the sum of the y components make the opposite side, and the sum of the x components make the adjacent side of that right triangle created with the vector. So this is a process you're going to be using in a worksheet coming up, and throughout this unit in particular, and in future units as well. There's a lot of adding complex vectors together in physics, so this is going to be your first intro to that. We normally make a table like this when adding vectors together, where we can list the values of our x components of each vector, our y components of each vector, the sum of the x components and the y components, the resultant, and the angle. So I'm going to give you a few examples of using this. Let's say that we have these two vectors working together and we want to find their sum. I don't really have to connect them tip to tail. I just have to find their x components and y components and add them together, and that will be kind of the same thing as connecting them tip to tail. So when I use vector math, I find that these are the x and y components of my vectors. So I'm going to write that down. It's important to remember that right and up in physics are considered positive and left and down are considered negative. Positive and negative are going to be really important here because there are going to be times when the vectors work against each other. So you're going to have to be very careful about noting which vectors are positive and which are negative. So I can see for vector A, I have 5 pointing up, so that's going to be positive 5 for its y component, and its x component is 8.7 pointing to the left. So I'm going to call left negative and label that negative to 8.7. And for B, I have 4.7 for my y component and 4.7 for my x component, and they're pointing right and up, so those are both positive. So the next step of adding these two vectors together is to find the sum of their x components and the sum of their y components. So that just means adding these two values together, and when I do that, this is what I get, -4 and 9.7. And so the total resultant, if I plug that into my square root formula, is going to be equal to 10.5. That's the total length of the resultant, and the angle is going to be equal to 67 degrees if I plug that in. And I can see that because the x component is pointing to the left, because it's negative, and the y component is pointing up, that 67 degrees is going to be in the second quadrant because it's negative for x but positive for y. So it would be right there. And that is what my sum of those two vectors working together would look like. A 67-degree angle vector with a magnitude of 10.5 in the second quadrant. Here's another example. Let's say that we have these two vectors working together. Again, I just need to find their x components, y components, and then add them together. So students get a little confused when they see that perfectly vertical vector and they're not entirely sure about what the x and y components of that would be. Because it's perfectly vertical, that means that it's not moving in the left or right direction at all, and so it's not going to have an x component. So ax would actually be 0 here, and ay would be -10 because it's pointing down. And then for b, when you find the x and y components, you find it's 7.5 and 2.7. So adding those two things together, the x component is 7.5 and the y component is -7.3. And when I put that into the Pythagorean theorem, I get 10.5 for r, and an angle of 44 degrees as my angle. And because y is negative and x is positive here, you can see that that would be in the fourth quadrant, because that's where y is negative and x is positive, and it's at an angle of 44 degrees. So that's how you solve problems like this. You're going to get a lot of practice with this, and it's going to be super important. When you have more vectors in a problem, when you have 3 or 4 or 5, you just need to make more rows for those vectors that you can then add together to get the total. But that's all that you need to know about complex vector addition. The best way to get good at it is just with a ton of practice. This is a quick video about 3D vector notation. We're not going to do too much complex math with 3D vectors. You basically just need to know when they appear and how they look and what they symbolize. So far, we've only worked with vectors in 2 dimensions, but we live in a 3-dimensional world. A dimension is an axis of motion that you can move on, and that is at a 90-degree angle to other axes. So something that's 1-dimensional has only one axis, like this, whereas something that's 2-dimensional has 2 axes that are at a 90-degree angle to each other, and something that's 3-dimensional has 3 axes that are all at 90-degree angles to each other like this. So again, 1-dimensional, 2-dimensional, 3-dimensional, which is what we're focused on today. So what do I mean by a 3D vector? Well, so far we've dealt with vectors that appear, if you were looking at this on your computer screen, like they could point up or down or left or right. A 3D vector would be a vector that could physically point out of your computer like this, or point into your computer like that. So how can we symbolize that? How can we use symbols on our 2-dimensional surfaces to symbolize 3-dimensional vectors? To come up with a symbol for 3-dimensional vectors, scientists looked at the vector and thought about where we got this symbol, where the symbol originated. And it probably originated with bows and arrows, like this. And so it's very easy for us to think about what a bow and arrow would look like if it were pointing up or down or left and right on the screen, but it can be a little more difficult to think about what a bow and arrow would look like if it were pointing straight at us or aiming straight away from us. So if the arrow is pointing straight at you, that's equivalent to the vector coming out of the page. Whereas if it's pointing away from you, that means that it's going into the page, like this. So thinking about how you would represent that with a picture, try to think for yourself about what you would draw to show what you would see if an arrow were aiming toward you or perfectly away from you. So scientists decided that the way that we would represent this is if it's pointing perfectly toward you, we'd have a dot that looks kind of like the tip of the arrow. And if it were pointing away from you, we would represent it with an X, because an X kind of looks like the fletching of an arrow pointing away from you, like the tail end of an arrow where the feathers or whatever you're using for stability go. So these are 3-dimensional vectors. They're not too intimidating. If it's a dot, that means it's a vector coming out of your page, and if it's an X, it's a vector going straight into your page. We can't really represent size with these symbols, and we don't even try to do that, especially not in this class. We only really represent sizes of vectors with 2D vectors. So if you see a dot on your screen, that means that it is a vector that is coming out of your screen like this. And if you see an X, that represents a vector going straight into your screen like this. So just as an example, this is what the symbol would look like in a lot of class problems. Here we have a wire, and you can see that to the right of the wire, there are vectors coming out of the screen pointing straight out, and to the left of the wire are vectors pointing straight into the screen, going into the screen like that. So that's 3D vector notation, which you will need a lot in this unit. This video is about the independent variable, dependent variable, control variable, and research question in a lab report. These are the first few things you have to fill out when deciding what your lab report is going to be about. We can start off with the independent and dependent variable. The independent variable is the thing that you control and change in an experiment, whereas the dependent variable is the thing that is affected by what you change. You measure the effects of the independent variable on the dependent variable. That's what your whole lab report is based around. How does the independent variable affect the dependent variable? As an example, we could pretend that we're doing an experiment where we're boiling different amounts of water and we're testing and seeing how long it takes those different amounts of water to completely evaporate away after we boil them. In that situation, the independent variable would be the amount of water that we're testing. We could test, say, 1 cup or 2 cups or 3 cups of water and boil that much at a time, and that's what we can directly control and change ourselves in the experiment. And the dependent variable would be the amount of time that it takes for the water to completely boil away, because that's the thing that we're testing that's being affected by our independent variable. So if we're testing how long it takes for different amounts of water to boil away, the independent variable would be the amount of water, and the dependent variable would be how much time it takes that water to boil away. Another example could be if we're running a race car, like a toy race car, down a track, and we want to see how much distance it will cover as a result of driving for a certain amount of time. The independent variable here would be the time that it's been driving for, because that's what we can control. We can control when it starts and stops, and so we can control how long it drives for. And the dependent variable would be the distance that it covered as a result of driving for that amount of time. So the independent variable would be time, and the dependent variable would be distance. One last example, we could imagine that we're growing plants with different amounts of water. So we're giving different plants different amounts of water and seeing how high they grow as a result. In this situation, the independent variable would be the amount of water that the plant received, and the dependent variable would be how high the plant grew as a result of that water. So it would be the height of the plant. So the independent is the amount of water, and the dependent is the height of the plant. The next definition you need to know is control variables. A control variable is anything that you keep constant in an experiment to make sure that it does not affect the results. Going back to our examples, in the example of boiling different amounts of water to see how long it would take to evaporate, we would want to make sure that the temperature that we're boiling the water at is the same for each experiment. Because if we also use different temperatures, then we don't know whether it's the temperature or the amount of water that's affecting how long it takes to completely evaporate. So we would want to keep the temperature completely the same. You may also know that water boils at different temperatures at different altitudes, so we'd want to make sure that we're testing the water at the same physical height above sea level. So those would be 2 control variables for that experiment. For the race car example, where we're testing how far it goes as a result of driving for different amounts of time, we'd want to make sure that the race car itself stays the same, that the track it's on stays the same, things like that, just things that would not impede it from moving the way that it normally would for a certain amount of time. For the plant example, we would want to make sure that we're using the same type of plant. So if we're comparing 2 completely different species of plant, that's not really going to tell us much useful information when we want to know how high they grow as a result of getting water. We'd also want to make sure that the plants have the same amount of sunlight, that they're in the same type of soil, things like that. These would all be examples of control variables. The last definition that you need to know is the research question. The research question is the question that your lab report is trying to answer. Your research question should always ask, how does your independent variable affect your dependent variable? So in your lab report, you're always going to have to write down a question like this, where you ask, how does IV affect DV? That's what the research question is. So in the water example, the research question would be, how does the amount of water being boiled affect the time it will take for the water to completely evaporate? In the race car example, the research question, how does the amount of time a race car has been driving affect the distance it has covered? And for the plant example, the research question would be, how does the amount of water that a plant receives affect the height that the plant grows to? So those are the definitions. These are 4 things you need to know at the beginning of your lab report. This is a short video about measurement uncertainty. There's a part of the lab report that asks you to explain your measurement uncertainty, so we're going to talk about what that means here. Measurement uncertainty is the result of imprecision in measuring devices. All measuring devices have some degree of imprecision and therefore some degree of uncertainty. Measurement uncertainty is always the larger of these two choices, either the limit of the instrument, which is half of the smallest increment, multiplied by the number of measurements taken, or a justified estimation of the limit of the measurement procedure as done by the experimenter. So let's see what that looks like in real life. We can imagine that we're measuring a pencil and we're comparing it to a ruler. So we need to use the limit of the instrument, half of the smallest increment, multiplied by the number of measurements taken. I can see that half of the smallest increment here, the smallest increment is 0.5 centimeters. I know this because I can see that there are lines for every centimeter and lines for every half centimeter. So the smallest space between 2 points that this ruler measures is 1/2 of a centimeter. So that's the smallest increment. So I'm going to end up using that in my equation. I now need to know how many measurements are being taken here. This is the part that confuses students a lot because they assume we're just taking one measurement. We're measuring the pencil once. But a measurement doesn't just mean measuring the actual pencil. When we're dealing with measurement uncertainty, a measurement is when we use the instrument and compare the instrument to the object. And when you think about that, we actually have to do that at 2 points on the pencil. We need to see how far it goes this way to the right and how far it goes this way to the left. So we're technically comparing 2 points on the pencil to the instrument. So we're taking 2 measurements here rather than 1. So therefore, the uncertainty is going to be that number of measurements times half of the smallest increment, which just turns out to be 0.5 centimeters again. So we would say that the measurement uncertainty of this ruler is 1/2 of a centimeter. And whenever we recorded any values that we measured from this ruler, we would record the values and add an uncertainty of plus or minus 0.5 centimeters to the end. As an example, if I recorded the length of this pencil, I would eyeball it and say it seems to be around 4.3 centimeters. So I would say that's 4.3 plus or minus 0.5 centimeters. So that's how we would record that based on the measurement uncertainty rules. Readings on a meter like this can also be a little strange. I can see that the smallest increment here is 0.2 volts. V stands for volts here, so 0.2 is the smallest space between 2 lines. And this is a little counterintuitive, but we would also say that we're taking 2 measurements here because we're comparing either side of this meter to the background measurements. So that's a little strange, but we would say that we're also taking 2 measurements in this situation. So for a lot of situations that you deal with, we would say that it's going to be half of the smallest increment times 2 measurements, which will just become the smallest increment again. So the uncertainty here would be 0.2 volts. So if I were to record this voltage, I can see that that line is around 3.3 or so. I'm not exactly sure. So I would record it as 3.3 plus or minus 0.2 volts. If you're working with a digital reading, the uncertainty will be at least plus or minus 1 digit of the last significant figure of the reading. As an example, we can imagine we have this digital scale, and right away I can see that the scale goes down to the tenths spot. There's 1 number after the decimal. So when I put this apple on it, I get a recording of a certain value, 136.4, in this case this is grams. And so the uncertainty here would be plus or minus 0.1 because it's plus or minus 1 digit of the last significant figure. And here that last significant figure is the 4 after the decimal point. So I would say its mass is 136.4 plus or minus 0.1 grams. So if you're writing a lab report and need to fill out the section explain the measurement uncertainty in the IV or DV, just write about how you followed this method. This video is about how to organize a data table. This is how the data table looks on your lab report. A data table is where you record the data from your experiment before displaying it as a graph. In IB Physics, all our data tables will look something like this. We can imagine for this video that the data table that we're making is for a lab where we are investigating how the mass of an object hung from a spring affects the stretch of the spring. So in this case, the independent variable would be mass, and I'm going to say that we're measuring mass in kilograms. So the first thing I would record is the title of my independent variable in the top left corner. So you can see I've recorded mass with parentheses kilograms. The reason why I'm putting the unit up there is so I don't have to write the unit next to each individual measurement that I make in the table below. As long as the unit is on the top, I know what all the units of each measurement are without having to write them over and over again in the table itself. And the dV here would be the stretch of the spring, and that's measured in meters, so I'd write that in the dV section. The plus or minus symbol in the data table stands for the measurement uncertainty of that variable. So I can imagine, for example, that I'm using a scale to measure mass that has an uncertainty of 0.001 kilograms, and I don't need to record that unit a second time because it's already recorded under the IV. And I'm going to imagine that the measurement uncertainty of my dV is also 0.001 meters. That's usually the measurement uncertainty on a meter stick. Above the table is a space to put the control variables. You've probably already written down the control variables in another part of your lab. Here you just have to copy them down a second time so you understand what's not affecting the data. So I'm just going to write down some imagined control variables for this experiment. Okay, I'm now going to make up some data. I'm going to imagine that as you were doing the experiment, you were trying to make sure that your independent variable went up by even increments. So I'm going to imagine that you go up by 0.05 kilograms at a time. So this is what your IVs would look like. So you would fill in your actual data here. This is where you would fill in the measurements that you actually took in your lab report. And in most labs that we do, you're going to take 3 trials of the dV for every IV value that you're measuring. So I'm going to fill those in as well. I'm going to imagine that this is the pattern that shows up. The next step after filling this out is to find the average dV for each row, which is really the average dV for every IV value. And the average dV means the literal mathematical average. And you may remember that the mathematical average is the sum of all your numbers divided by the number of numbers that you're adding. So here you would add up the 3 trials and then divide by 3. So in that first row, you would add 0.012 plus 0.010 plus 0.008, divide by 3, and the answer that you get is 0.010. So that would be your average dV measurement for that IV. Usually we record the unit a second time here. The unit of your average dV is the same as the unit of your regular dV. The next step is to fill out the statistical uncertainty. The statistical uncertainty is uncertainty that you have about your data based on how far apart your measurements are from each other. As an example, if I stepped on a scale 3 times and the first time it said I was 180 pounds and the second time it said I was 181 pounds and then it said I was 179 pounds, I would feel pretty certain about my weight. That range of data would give me a lot of certainty because the numbers are so close to each other. Whereas if I stepped on the scale and it said I was 10 pounds and then I stepped on it again and it said I was 1,000 pounds, that would introduce a lot more uncertainty. So the farther away your numbers are from each other, the farther away your measurements are from each other, the more statistical uncertainty you have. So the formula we use to find that statistical uncertainty is the largest number in your range, that's the largest dV in this case, minus the smallest number in your range divided by 2. So as an example, if the largest number in a range were 6 and the smallest number were 2, 6 minus 2 is equal to 4, and half of that is 2. So we would say that if the largest is 6 and the smallest is 2, the full range is 4 plus or minus 2. So that 2 would be the statistical uncertainty. So we're going to take the largest trial minus the smallest trial divided by 2. This is an example for that first row where the largest is 0.012 and the smallest is 0.008 divided by 2, and this is what we get. So those are the statistical uncertainties, and we usually also record the unit that statistical uncertainty is measured in the box above it. Finally, we need to find the error bar values. The error bar values are something that we'll use when we're actually graphing the data. We'll talk about that more in the Logger Pro video. For now, you just need to know that error bars express uncertainty. So when we're drawing error bars, we want to make sure that we're expressing the full uncertainty that we actually have. And that would be the larger of either the statistical uncertainty or the measurement uncertainty of the dV. So whichever number is larger is the one that I'm going to record in my error bar. So in that first row, I can see that the statistical uncertainty is 0.002 and the measurement uncertainty back in my dV box is 0.001. 0, 1. So statistical uncertainty is bigger. So that's what I would record in my error bar value for the first box. And here the statistical uncertainty is always bigger than or equal to the measurement uncertainty. That's just a coincidence for this lab. So I would record those values specifically. I just compare statistical to measurement and see which one's bigger. Here's an example where the measurement uncertainty is bigger than the statistical uncertainty, and so the error bars would be entirely the measurement uncertainty numbers. It's just whichever one is bigger. The last thing that you need to know about data tables is which part of the table you will take with you to your graph, which parts of this table you will actually graph. So this section and this section is the part that you will not graph. The reason why is that these sections really exist to get you to other sections of your data table. The only reason you take the trials is to get to an average DV measurement. And the only reason you find the statistical uncertainty is to get to your error bar value. So these things are not actually going to graph. The IV always goes on the x-axis of our graph, and the DV always goes on the y-axis, the vertical axis. So these values are what you would put on your x-axis. These values are what you would put on your y-axis. You'll want to also label your x-axis with the name of the independent variable and label your y-axis with the name of the dependent variable. In IB, we do something very specific where we give the name of the variable and then put a dash and then put the unit. So we don't use parentheses for the unit. So if I were writing the x-axis for this graph, I would title it mass dash kilograms like that. And if I were labeling the y-axis, I would call it stretch dash m for meters. So this is what that would look like. When you're creating your graph in Logger Pro, you're going to need to add error bars in both the x direction and the y direction. In the x direction, the error bars will just take the value of the measurement uncertainty. And these are the y-axis error bars. So when you calculate error bars, you're really calculating for the y-axis specifically. And that is everything that you have to know about data tables. In this video, I'm going to show you everything you need to use Logger Pro throughout the entire year. Logger Pro can seem complicated at first, but it's actually a really simple tool, and we'll only be using a few parts of it throughout the whole year, and they'll all be covered in this video. And so if you can understand what's covered in the video, you'll be good for the rest of the course. Logger Pro is designed to create graphs out of sets of data, which will then allow us to create maximum and minimum lines of best fit that are very precise. We want those for our lab reports, so that's what we're going to be using Logger Pro for. Basically, we'll make a graph, put error bars on the graph, and then make a max and min line of best fit. So the first thing I want to know is how to actually make a graph on Logger Pro. When you make a new graph, it automatically comes with an x-axis and a y-axis, and a column right here on the top left for the x and the y numbers. I'm going to fill those in just a second, but before I do, I'm going to show you how to change the names of those axes, because we're not really going to be using x and y as our axes titles for each graph. We're going to be using things like height, position, speed, temperature, things like that, actual things that we're measuring about the world. So we're going to want to change the title of those axes before we actually do anything with them. So to change the title, you can just double click on this square, and that brings up this menu. If you go to column definition right here, this will give you all the important steps to actually naming and titling the column. Just as a heads up, these buttons probably look a little bit different on my computer than they do on yours, just because I'm using a Mac, but they're all in the exact same position in your version of Logger Pro. They just have slightly different symbols than on mine. So let's say that I'm making a position time graph. In a position time graph, time goes on the x-axis, so that's what I'm going to title this. And the short name for this is just the symbol that takes this spot if this name is too long to fit in a position. So the short name for time I can just say is t, and the units of time are seconds or lowercase s. So that's what I would enter in for this column. I'm not really worried about anything else, don't really want it to be any other data type, just keep it as numbers, click done. So now my x-axis is changed to time. Now my y-axis, going to make that position, short name P, units M for meters. And I also want that to be numeric, not a date or anything like that. Okay, so I now have my axes ready and I can start to enter numbers into my table. I'm going to imagine that I did an experiment and tested time equals 1, 2, 3, 4, and 5 seconds. And I'm just going to make up some numbers for the position. Let's say that the position is just increasing similarly. So I'll just do 4, 8, 12, 16, 20. You can see that as soon as I type these numbers, dots appear on my graph. So this is a graph of the data that I just entered in there, if this is the y-axis and this is the x-axis. Now, there are two ways to scale this graph so that the data takes up more space so you can see more of it. You can either drag your mouse down here until it makes this double arrow symbol and drag back and forth. That physically moves where the graph is. If you go to the far right, it turns into the single arrow symbol. That stretches and compresses the graph. That's one way to fit the data to your graph, but there's actually a much simpler way. If you go up here and click this A button in the graph, that auto scales it, so it automatically stretches out the data to take up as much room as possible. So you're always going to want to do this when working with a graph. So that's how you put data on the graph. If you want to change which axis is graphing what, you can go and click on the name of the axis, and it gives you the option of using a different data table. So if I want to use position for the x-axis, I can just go here, click position, and now position is also on my x-axis as well. So I'm going to go back to time for now. So that's how you change what each axis is graphing. Let's imagine that we have error bars for these sets of data. We want to put on a certain amount of error that both the x-axis has and the y-axis has, just because that's going to be pretty common in the experiments. So to make error bars, I'm going to need a separate table to tell the program what values the error will take. What values of the error bar am I taking from my data table? So I'm going to go to Data and click New Manual Column. This is going to add in a new column right here, and the reason why I'm choosing manual and not calculated is that this just means I'm going to enter in the numbers by hand. This is for when you want the computer to calculate the numbers for you, which I'll show you how to use in just a minute. So let's say that I want to calculate the time error, or I want to show the time error bars on this column. So I'll call this time error, and I'll call the short name TE for the error in time. And the units of error are the same as the units for the thing being measured itself, so that's going to be seconds. Hit done. And so now I have this new column. And you'll notice this doesn't show up on the graph because I haven't told the graph that one of the axes is the time error. So let's imagine that my measurement uncertainty for time on my data table is 0.4, and that's going to stay the same for all the measurements. So I'm going to enter in manually 0.4 for each part of the column. So if this is my error and I want to represent it as error bars on the graph, what I'm going to do is go back to time, the thing that you want the error bars to be on, go to Options, and then click Error Bar Calculations, this checkbox right here. You can either choose a constant, so I could just tell it that all of these points are going to have plus or minus 0.4, and that will actually put the error on my graph for me. If I go back here, I can also just say to use a column. So if I made a column of error like I did right here, I can just select which column I made, time error, and it will use each of these numbers for each of these points. So this is useful if you want some error bars to be bigger than others. If you have one number that has more error, like let's say that this has an error of 2, it will automatically adjust that particular error bar, but not the others. So getting to use a column instead of just a fixed error allows you to change the individual errors on each point. But I'm going to keep all of these at point. I'm going to do the same thing with the y-axis. I'll say new manual column right here. Say position error measured in meters. And I'll just make up some numbers for this. Let's say that we have an error of plus or minus 2, or just plus or minus 1, actually. 2 would be a little big. So I can go back to position because this is the thing that I want to put the error bars on. Double click, go to Options, Error Bar Calculations, Use Column. And so I just made my position error column with all the error values for that. So I can click on that. And now the error bars show up here as well. So this is really good. This is most of what I want to use Logger Pro for. There are just a few more tools that I need to show you. The last step of creating a graph in physics is always putting the maximum and minimum lines of best fit onto the graph so that you can understand the biggest and smallest possible line you can get out of this graph. To do that, you're going to click on this last picture of the lines right here where it says curve fit. You don't want any of the others. Just click curve fit. Now, this gets a little complicated. Just pay close attention. You're going to go to Manual, which basically means you're going to get to control the line itself. And make sure you have a linear line selected. You don't want a quadratic line or anything else. If you can't see this line show up in this picture, that might mean that the slope is either too small or too large. You can change the slope of this line right here, and it doesn't really matter what the slope is as long as you can physically see it on your graph so that you can start to manipulate it. For example, if the slope is 0.0001, the line immediately disappears. You can't see it, so you're not going to be able to work with it and drag it along your graph when you hit OK. So you just want to make sure it's something you can see. As long as you can do that, then the M and the B don't actually matter very much. So I'm going to select 1 and 1. And when I do that, this line appears on my graph. I want to be able to drag it around and make a maximum and minimum line of best fit for my graph. To be able to physically move it around the graph, I'm going to go up here, double click on this box, and go to the bottom right here where it says Enable Line Drag. When I click on that, these diamonds appear on either side of the line, so now I can physically drag it along my graph. These two control the slope, and this middle one right here controls the up-down position of the line. So let's say that you want a maximum line of best fit. To make a maximum line of best fit, you want it in the bottom right corner of the square of uncertainty down here, so that's about right here. And in the top, you want it in the top left. That'll make it as steep as possible. If I want to make this a little more clear, I can also drag this graph down a little bit so I can see where this is a little bit better. I would say that that's my maximum line of best fit. That is the steepest line that I can get that goes through all of these error regions. If I made it any steeper, it would no longer go through some of these boxes. Like if it were up here, it would no longer be going through this one, so it's not actually a possible line for my graph. You'll notice that this gives you the slope and the y-intercept of this line. So when your lab reports ask you for what is the slope and y-intercept of the maximum line of best fit, this box right here is where you're going to get that from. My slope is 5.275 and my y-intercept is negative 3.969. So that's where you get the numbers from for your maximum and minimum line of best fit equations. So this is my maximum line of best fit. So now I'm just going to add another line in the same way, go to manual and make my minimum line of best fit. So it's still linear. I can still see the line, so I don't need to adjust the slope at all. I hit OK, go over here, enable line drag, and now I can move this around like this. Okay, so I would say that this is my minimum line of best fit. So that's basically like 95% of what you need to know about Logger Pro right there. There's just a little bit more information you're going to need to know just to do something very specific with Logger Pro, which is linearization. If you don't know what linearization is yet, that's totally okay. I just need to show you basically one more small tool that you can use to figure out some more information. And that's going to be making a new calculated column right here. This is the very last thing that you need to know about Logger Pro. Let's say that we're doing something specific to our time measurements to change the shape of the graph. Let's say, for example, that we want to square our time values, but we don't want to do that by hand. We can just have the computer do that for us to avoid having to do calculations. So if instead of graphing position versus time, I want to graph position versus time squared, I can go to Data, New Calculated Column. I'm going to name this new column Time Squared. And the short name will be T squared. And if we're squaring time, the units of that are going to be seconds squared. So to carry out a formula on a set of data, you just need to go to Variables, select the column that you would like to perform the function on, and then write out what you want to do to that function. So in this case, I want to square time. So I hit Done. And now I have a new column of all the time values squared. My original time values were 1, 2, 3, 4, 5, and so my new time squared values are 1, 4, 9, 16, and 25. If I want to graph this, I can just go down here and tell the machine to graph time squared instead of time. Obviously, this makes my graph look pretty weird, but this is what it would come out to if I graphed time squared instead of time. Obviously, if I wanted to put a new error on these lines, I could just make a new column, time squared error. I'll just make up numbers for right now. I can just go over here, error bar calculations, use column, time squared error. And so I could add error bars there as well. So if you want to make a new calculated column of numbers, you just go here, select new calculated column, and then just write out the equation that you want to perform on your variables. And that's it. That's literally everything that you're going to need to know about Logger Pro for this entire course. So as long as you can just stick to those functions, you'll be good. Now that you're done making your graph on Logger Pro, the next step of your lab report is to find the average line of best fit from your max and min lines of best fit. So a line of best fit is a straight line that best represents the data on a scatter plot. The line does not have to pass through every point to best represent the pattern of the data. So you can see that even though this line that's drawn on this data is not actually physically passing through every point, it still does a pretty good job of predicting where that data is going to appear. So that's the goal for a line of best fit. The goal for a lab report in general is to predict what will happen in the future, or predict what will happen for quantities that you haven't tested yet. And the way that you can do that is by using a mathematical line like this to find what the value of that line will be for quantities that you haven't tested. This is another example of a line of best fit. One thing to say before we start, if you're drawing your physical graph on your lab report, do not connect the dots on your graph. This is completely meaningless and gives us no useful information at all. So please don't do that as you're drawing this. So by now you've added error bars onto your LoggerPro graph, and those error bars create areas of uncertainty where your data could possibly be. And you've drawn a maximum line of best fit through those areas of uncertainty, and you've drawn a minimum line of best fit as well, lines that have the largest possible slope and the smallest possible slope that can still fit through most of those areas. So our idea is that if that's the biggest possible line you can get out of this data and the smallest possible line you can get out of this data, the most reasonable estimate for what your data is actually doing, the line that your data is actually on, would be something right in between the minimum line and the maximum line. So if we can find the average of those two lines, then we'll have the best estimate that we can get of what your data is actually doing. So now we just need to understand how to actually take the average of two lines. So the first step in taking the average of two lines is to write the equation for both lines. There's a space on your lab report that looks like this. This is where you're going to physically copy down the equation for each line. And to get the equation for each line, you're going to need to use LoggerPro. These four spaces specifically are where you're going to fill in the information that you get from LoggerPro. Everything else you can fill in from previous parts of your lab report, but these four spaces you're going to need to use the equations that you got for that maximum and minimum best line, for that maximum and minimum best fit line. So the boxes for the manual fit lines that give you the slope and y-intercept for the max and min lines look something like this on LoggerPro. So you're going to take the slope of your maximum line and the y-intercept of your maximum line and put them here and here, and the slope of the minimum line and the y-intercept of the minimum line and put them here and here. You'll notice that most of the time the y-intercept of the minimum line is actually going to be larger than that of the maximum line. This makes sense if you think about it as having the smallest possible slope. So I'm going to copy down these numbers here. And you don't have to copy down every single number that LoggerPro gives you. Round to a reasonable number of significant figures based on your original measurements. Okay, this is everything that you have to fill in. The y variable is just another name for the name of the dependent variable. The units are the units that dv is measured in. The slope unit is going to be the dv unit over the iv unit, just because slope is rise over run. And on a graph like this, we're measuring the dv on the y-axis and the iv on the x-axis. So the slope units will be the units of dv over the units of iv. The x variable is the independent variable, so you'll just copy down the name of that variable, and the x unit is just going to be the unit of IV. And finally, the y-intercept units are also going to be the dv units, the dependent variable units, because if you think about it, the y-intercept is going to be measured using the units of the y-axis. So I'm going to imagine that we're comparing displacement and time. So displacement measured in meters is our dependent variable, and time measured in seconds is our independent variable. So those would go where they go. You can see that the slope units are the unit of the dv over the unit of the iv. So here that would be meters in the numerator and seconds in the denominator. So that's how we would fill out the equation for the maximum and minimum curves of best fit. Okay, the next section of the lab report asks you to find the average of the slope and the y-intercept and the absolute uncertainty of the slope and y-intercept, and sometimes it will also ask you for the percent uncertainty of one or the other. These are the equations that you need to use for each one. These equations are also given to you on the left in those boxes. You can see as an example below average value, it shows sum over the number of values. That's the equation for the average of numbers. I'm just giving them to you like this so it's a little more clear what you have to do. So you can see that as an example, to find the average slope, you add the slope of the maximum line plus the slope of the minimum line divided by 2. So it's literally the mathematical average of the two slopes from your experiment. And the absolute uncertainty is going to be the largest slope minus the smallest slope divided by 2. Based on how we've been using uncertainty in previous parts of the class, that makes sense. It's just half of the range of the possible values that that slope could take. If I take that max and min line of best fit equation that I got in the previous slides and plug in the slopes and the y-intercepts to their correct spots, these are the numbers that I would get for each value. Finally, the percent uncertainty of the slope is just the absolute uncertainty divided by the average slope times 100. So I'm just going to take those numbers and multiply them by 100%, and that will be my slope uncertainty. So here it's 22% uncertain. The next step is to get the average best fit equation itself. And this is kind of one of the big central goals of the lab report. If you can get an equation that tells you what value your dV is going to take for any IV, you've found a way of basically predicting anything that will happen in your experiment, which is a pretty big accomplishment. The goal of all science is to predict things. The goal of physics specifically is to predict motion. And so if you have an equation that can make a prediction for any independent variable and tell you what the dependent variable will be, that's a huge accomplishment. So let's see how we fill in this average curve of best fit equation. This is what you're going to put into each section. The y variable is the dependent variable. The y units are the dv units. The slope of this average line of best fit is going to be the average slope that you calculated in that previous section. The slope uncertainty is going to be equal to the absolute uncertainty of the slope. The slope units are the dv unit over the iv unit. The x variable is the independent variable. The x units are the units of the independent variable. The y-intercept is going to be that average y-intercept that you calculated. And you're also going to include the y-intercept uncertainty and the y-intercept units. So here, these are the units that I used in my experiment, and these are the numbers that I got from the previous section. So this would be my average curve of best fit equation. This equation is telling me that if I plug in any time, I can multiply it by 3.2 plus or minus 0.7 meters per second, add negative 0.7 plus or minus 4.3 meters, and that's going to give me a specific displacement as a result. And so that's how you create the average line of best fit from the maximum and minimum lines of best fit that you get from Logger Pro. This video is about the proportional reasoning section of a lab report. Proportional reasoning is going to be a really gigantic part of this class moving forward, and there's a lot to say about it and a very specific method for dealing with it that we're going to introduce a little bit later in the year. For now, I'm just going to give you the basics of how to fill out this one section of a lab report. Basically, the goal is to understand what will happen to your dV if you perform certain mathematical functions on your IV. So if your IV doubles, what will your dV do? If your IV triples, what will your dV do? If you divide your IV by 2, what will happen to the dV? So we're going to see how we can figure that out. Before beginning, you should fill in each blank spot with IV and dV with the names of your experiment's IV and dV. So I'll use a time and position experiment as an example. That's pretty straightforward, so we're just trying to understand if we do something to time, what will happen to the position as a result. What you fill in for the question mark sections will depend on the pattern of your graph. To figure out what to write, you should follow these steps. You should start by writing your equation for the pattern of your graph with your variables. Next to the equation, write a new equation where you perform the function on the IV. As an example, if you triple the IV, write it as 3 times your IV. Then carry out the math so that you have the original equation for dV multiplied by a constant, and that constant tells you what's happening to the dV. This sounds pretty complicated, but if I go through step by step, I think you're going to see that it's actually pretty simple. So let's imagine that we've identified our graph as linear. We've looked up at the patterns posters and seen that there's a linear pattern to the graph. So I know that the equation for linear graphs is dv is equal to some constant times iv. In this case, position is equal to some constant m times time. So if I triple the IV, I want to know what happens to dV. That's one of the questions in the proportional reasoning section. So this is what it's going to look like. We're going to get some new position as a result of multiplying our time by 3. We're tripling the time to see what happens to the position. And if I isolate the original equation is just position is equal to m times time. And now I have m times 3 times time. So if I pull out that 3, I've now isolated the original equation in this new equation. Because I can see that m times time is equal to the original position that I had before tripling this number, I can see that the new position of the object is going to be 3 times the original position. So that means that the new position has also tripled. So if you triple the time, the position will triple. With linear equations, this is pretty straightforward. You can see that if I have the time specifically, if I divide the time by 1/2 and isolate that, you can see that the position is also being multiplied by 1/2. So the position will also be halved. We can go on to a different type of function. Let's say that instead you've identified the graph on LoggerPro as being a quadratic graph using the equations posters that we have. So a quadratic graph behaves like this. That's the base equation. The dv is equal to some constant times the iv squared. So let's see what happens if we triple the IV. So there's some new position that's equal to a constant times 3 times time squared. That all has to be inside the parentheses because the IV itself is being tripled and the whole IV is being squared. And when I have two numbers inside of a square like that, I have to carry out the square to both sides. So I get that the new position is equal to a times 9 times time squared. So I can isolate a times time squared and see that the new position is equal to the original position times 9. So I would say if you triple the time, the position is now multiplied by 9 if this is a quadratic pattern. And I can try halving it as well. So I can multiply the time by 1/2. Carrying out that square gets me 1/4, 0.25. Isolating a times time squared gets me that the new position is equal to the original position times 0.25. So that's the same as dividing by 4. So that's what will happen to the position if you have the time, if this is a quadratic graph. Another example, we can imagine that you've identified it as being inverse, and this is the pattern that inverse graphs follow. The dv is equal to some constant times 1 over the iv. So if you triple the iv, this is what happens. You can see that I've now isolated position times 1/3, so the new position will be 1/3 as big as the original if you triple the time. And if you have the time, you can see that the new position will be multiplied by 2, which is the same as being doubled. Just one thing to note, if you're working with a linearized graph, and if you don't know what that means yet, we're going to talk about it, you should answer the proportional reasoning section about the original graph, not the linearized graph. And that's what you have to know about proportional reasoning. This video is going to be about the physical meaning of the slope and y-intercept of your graph. There's a part of your lab report that asks you what the slope and y-intercept physically tell you, so this video is going to help you figure out what they mean. So we know that the slope of a graph is the rise over run, or the change in your y value divided by the change in your x value over a given length of the graph. And because the value of the slope is the change in y over the change in x, the unit of slope is the y-axis unit divided by the x-axis unit. As an example here, I can see that I have a graph that has mass on the x-axis measured in kilograms and stretch on the y-axis measured in meters. So if I take the slope of this graph using the equation for a slope, I can see that the unit that my final answer will be in is meters per kilogram, meters over kilograms. In this case, this is 6/6 meters per kilogram, or 1 meter per kilogram. So even just saying that unit out loud, meters per kilogram, kind of gives you some idea about what the meaning of the slope itself is. Just to make it completely clear, this is what the slope always means in a lab report. The meaning of the slope is always how much does the dv change for every 1 unit of change in the IV. Another way of saying that is what is the rate that dv changes per unit IV. So as an example, we could imagine that this is a graph of a baby's weight over time according to its age in months, and its weight is measured on the y-axis. And I can see that the slope has a value of 2 pounds per month. So that means that the physical meaning of this slope, because the meaning is how much does the dv change for every 1 unit of change in the IV, here the meaning of slope is for every month that passes, the baby gains 2 pounds. So just the unit pounds per month gives you a pretty good idea of what the slope itself means. So you can use the unit of slope to understand what it means. Here's another example. This is a position time graph, and position is measured in meters and time is measured in seconds. That means that the slope is meters per second. The slope here is 2 meters per second, which means that the object is moving at 2 meters for every 1 second that passes. For every second that passes, the object moves 2 meters. So that's the physical, real-world meaning of the slope of this lab report graph. One last example, here I can see that we're measuring the temperature of an object in degrees Celsius per time that has passed in hours, and the slope is negative 1.5 degrees Celsius per hour. So the meaning of that slope is that the object is losing 1.5 degrees Celsius of temperature for each hour that passes. So that's how you understand the meaning of slope. The meaning of the y-intercept is even more straightforward. The meaning of the y-intercept is always what was the dv value when the IV was 0, because the y-intercept is the y value when the x value is 0. As an example, going back to the graph of the weight of the baby per age, I can see that the y-intercept is 6 pounds, which means that when the baby was 0 months old, the weight was 6. So a more everyday way of saying that was that when the baby was born, it weighed 6 pounds. So that's the physical real-world meaning of the y-intercept. What the y value is when the x value is 0. What the dv is when the IV is 0. Another example with the position and time situation, you can see that the y-intercept you can see that there the y-intercept is 1 meter, so that means that before any time has passed, the object is already 1 meter ahead of wherever we're considering the 0 point to be. So the object was at a position of 1 meter when the timer started. For your last example with temperature, I can see that the y-intercept of the temperature graph is 20 degrees Celsius. So that means that before any time passes, the initial starting temperature of the object was 20 degrees Celsius. So those are some examples of how you get the physical real-world meaning of the slope of your graph and the y-intercept of your graph. This video is about distance and displacement. So distance is the total scalar length of the actual path that an object moved. The variable we use for that is d, and the unit is m for meters, whereas the displacement is a vector that points from where the object started to where it ended, regardless of the specific path that it took. In IB physics specifically, we use the variable s for displacement, and the unit is also in meters. Here's an example of what I mean by distance and displacement. Let's say that we have a person who moves in this path. They start here, they walk 3 meters up, 3 meters to the right, and 3 meters down, and they end there. So the total distance is equal to 9 meters. That's the total length of the actual path that they actually traveled. Whereas the displacement is just a vector that points from where they started to where they ended and completely ignores the path that they took to get there. So here I can see that the displacement is definitely 3 meters to the right. When they're ending, they've kind of canceled up their up and down motion, and so they've moved 3 meters to the right, but nothing else. So the displacement here would be 3 meters to the right. It has that direction as well because displacement is a vector. Here's another example. Let's say that a person moves like this. They move 3 meters up and then 4 meters this way. Their total distance is 7 meters because they just moved 3 meters and then 4. And their displacement is going to be this straight line here. So I need to figure out a way of finding that length of that straight line, and you may be able to guess that this is making a right triangle. So in this case in particular, to find the displacement, we would use the Pythagorean theorem. Plugging in our numbers gets me a total displacement of 5 meters. That side has a length of 5 meters. And I wouldn't expect you to get the exact angle for that displacement. We don't really go that far into displacement specifically. So I would just say that the displacement is 5 meters up and right. Here's another example. Let's say that they move like this. They just move 6 meters to the right like this. So obviously their distance here is just 6 meters, and their displacement is actually also going to be 6 meters, because if we draw that straight line here, the two things happen to be equal. So displacement is 6 meters to the right. So you may have noticed, based on this pattern, that distance can be bigger than or equal to displacement, but it can never be smaller than displacement. One more example. Let's say that they move like this. Here they've moved forward 6 and then backward 6, and they ended. And so their total distance is 12 meters. And if we were to draw a vector from where they started to where they ended, the vector wouldn't have any length because the start and end point are the same. So we would say that the displacement is actually just 0 meters. When we're dealing with motion on an axis, we need to define a 0 point where we measure everything else from, and a positive and negative direction. Both of these are arbitrary. You can choose for yourself which direction is positive and negative and where the 0 point is. So I'm going to choose 0 to be right here, and these will be my positive and negative directions. And these will be my numbers. So I'm going to have this person move along the number line and observe the differences in their distance and their displacement. So I'm going to have them move up here to positive 5 meters, and I can see that their displacement was positive 5 and their distance was also positive 5. I'm now going to add a second distance and a second displacement and say they move back here to 3 meters. So because they're moving in the opposite direction of the positive direction, their displacement is going to have to be considered negative because they went from 5 down to 3. So if displacement is negative, that just means the object is being displaced in the negative direction. Distance can never be negative because it's a scalar. It has nothing to do with direction. It's always positive. So here, the displacement would be negative 2 meters and the distance would be positive 2 meters because you just moved another 2. And after I add those two motions together, I can see that the total displacement is 3 meters, and the total distance traveled was 7 meters. And I can see that those sums work for the two individual distances and displacements. So the way that we add them kind of fits the definition of distance and displacement themselves. Because displacement can add or subtract, if you backtrack, you're going to get closer to where you started, and so that's going to decrease your displacement. Whereas if you just move back and forth, you're always increasing your distance no matter what, because the distance is always positive. We can also flip which side is positive and which side is negative and still get very meaningful results. So if I perform this exact same motion, I can see that the only real difference here is which direction is being considered positive and negative. So this is saying I have a displacement of negative 3 and a distance of positive 7, and I can see that that's true because right is negative, so this is still describing that same exact motion as before. We're just using different symbols to describe it. So this is one reason why which side you choose as positive and negative is totally arbitrary here. So that's how you use the concept of distance and displacement to describe motion. This video is about speed and velocity and the difference between them. Speed is the distance that an object travels divided by the time that it takes to travel that distance, and it's a scalar because it depends on distance. Velocity is the displacement an object travels divided by the time it takes to travel that displacement, and because it depends on displacement, it's a vector. A quick note on the unit, the reason why we use meters times seconds to the -1 is that that's equal to meters per second, which is a more common way of saying that unit. The reason why that unit is what it is because both speed and velocity is a distance or displacement in meters divided by a time in seconds. For example, if you walk 4 meters in 1 second, your speed and your velocity is 4 meters divided by 1 second, which is equal to 4 meters per second, or 4 meters times seconds to the power of -1. That's how we write it in IB specifically. That speed can work for different distances in time. For example, if we cover 8 meters and it takes us 2 seconds, that's 8 meters for every 2 seconds, which again comes down to 4 meters per second when we divide it out. Here are a few examples of using the equations for speed and velocity. We can say this person starts here and moves like this, and you can see that 3 seconds have passed in total by the time they get to the end of their motion. So the distance covered is 9 meters, and I can see that the displacement is 3 meters to the right So we can use these values to solve for both the speed and the velocity. And the speed is going to be the distance over the time, which is 3 meters per second. And the velocity is going to be the displacement over the time, which is 1 meter per second right. So that would be the difference between speed and velocity in that case. Here's another example. We can imagine this person walks like this and ends there. And this is a case where the distance and displacement are the same length. Displacement just has a direction. And so the speed and velocity would have the same magnitude. They'd have the same size, 3 meters per second. It's just that the velocity would have this direction as well. This is example number 3. Here we have this person starting here, walking forward, and then walking backward like this. So altogether, I can see their total distance is 12 meters. But their displacement is 0 meters because they ended at the same place where they started at. So that means their speed would be 3 meters per second because it took them 4 seconds, and their velocity would be 0 because altogether they stopped at the same place they started, so the total velocity would be 0 meters per second. Just a quick note, if velocity is negative, it means that the object is traveling in the direction we've defined as negative. So as an example, if this person walks from 7 meters to 0 meters like that, the speed would be 7 meters over 1 second, but the velocity would be negative 7 meters over 1 second. And so the speed would be positive 7 and the velocity would be negative 7. So the positive and negative allows us to express direction with velocity. That's all that it means really. Negative just means moving in the negative direction and positive means moving in the positive direction. And we define what those are. Whereas with speed, speed is always recorded as being positive. It doesn't have a direction. It's just always positive. This video introduces the idea of acceleration. So before we start talking about acceleration, I just want to remind you that the triangle symbol delta means a change in math and science. So as an example, delta V means the exact amount that velocity has changed. It's the literal number amount that velocity changes by. I'm also introducing 2 new variables before we start talking about acceleration. U is now going to stand for the initial velocity or the starting velocity of an object, and V is going to stand for the final velocity of an object at the end of a problem. So we can now start talking about acceleration. So acceleration is the change in an object's velocity divided by the time the change takes place. Acceleration is a vector. The variable for acceleration is lowercase a, and the unit is meters per second squared, or meters seconds to the -2. I'll explain why that is a little later in the video. So the equation for acceleration is the change in velocity over the time that has passed. And the change in velocity is going to be equal to the final velocity minus the initial velocity. So just as an example, if your final velocity is 5 meters per second and your initial velocity is 2 meters per second, the change in your velocity is the final minus the initial, or 3 meters per second. We'll start with an example problem for this equation. So we have a car accelerating from rest at 10 meters per second squared for 6 seconds. What is its final velocity? I'm going to plug this into the guess method. So I'm going to write down my given information. I can see that the starting velocity is going to be 0 because the problem says that a car accelerates from rest, so from a velocity of 0. And the time that it takes to accelerate is 6 seconds, and the acceleration itself is 10 meters per second squared. So we want to know what its final velocity is. So our unknown is the final velocity. Obviously, the equation that we're using to connect these is the acceleration equation that we're learning now. So now I want to solve this equation for the final velocity. So I just need to isolate that v, so I'm going to multiply both sides by t. Those cancel out. And I'm left with the final velocity is equal to acceleration times time plus the starting velocity. I'm now going to substitute and put in the numbers that I have. And when I do that, I find that the final velocity is 6 meters per second. So this kind of makes sense because if the acceleration is 10 meters per second squared, that's the same as saying 10 meters per second per second. So every second that passes, the velocity is going to increase by 10 meters per second. So if it's starting from 0, after 1 second, it's going to go at 10 meters per second. After 2 seconds, it'll be going at 20. After 3, it'll be going at 30 meters per second until 6 seconds have passed and it's going 60 meters per second. So just to visualize this with a velocity vector, again, after 1 second, it's going at 10 meters per second. After 2 seconds, it'll be going at 20. And by the time we get to 6 seconds, it's going at 60 meters per second. One misconception about how this acceleration happens is students sometimes imagine that when something is accelerating, it's going at a constant velocity each second. It's just a higher velocity every second. So it starts off at a constant slow velocity for 1 second and then gets faster and faster and faster and faster and kind of jumps to the next velocity like that. But that's not really how it works. The correct understanding is that it's kind of one continuous increase in velocity. It just gets faster and faster and faster instead of kind of jumping up the velocities like that. So just to visualize this with a speedometer, the misconception is that every second the object is just getting exactly 10 meters per second faster and just jumping up like this every second. But this is not what's happening. Instead, what's happening is just a continuous increase where every second, every full second, the velocity is exactly 10 meters per second faster. So this is what it would actually look like. Just one continuous increase where every full second leads to a 10 meter per second increase in velocity. A lot of students are also confused about why acceleration is a vector. The reason why acceleration is a vector is that acceleration is a change in velocity, and velocity is a vector. To show how velocity changes over time, we need to use another vector to add that change to the original vector. So as an example, if at a time equals 0, our initial velocity at 0 is 10 meters per second, and after 1 second has passed, the velocity is now 12 meters per second, that vector is that much bigger. So we can describe the change in velocity as itself being a vector. If we connect the tip of the original velocity to the tail of the change in velocity, we can use vector addition to see how the velocity is changing into that new velocity. So that red vector of 2 meters per second to the right is the change in velocity. And because acceleration is the change in velocity divided by time, that's also going to be a vector. Here that's just 2 meters per second squared to the right. The direction of acceleration matters for how the velocity changes. If the acceleration points in the same direction as the velocity, the object will speed up. And if the acceleration points in the opposite direction as velocity, the object will slow down. To build up your intuition on this, I'm going to draw a black vector to symbolize the velocity and a red vector to symbolize the acceleration. So I'm going to imagine that every second the object is getting this much faster, the acceleration vector faster. So if I add these vectors tip to tail, I can see that the new resulting velocity after 1 second is going to be this long. So because acceleration is pointing in the same direction as the velocity, it's making the velocity bigger over time. So this tells you that if the acceleration points in the same direction, the velocity is getting bigger, and if the velocity is getting bigger, that also implies that the acceleration is pointing in the same direction as the velocity. So it works in both directions that way. So let's compare this to slowing down. If an object is moving fast but slowing down, the change in its velocity, if I connect it tip to tail, is going to be working against that original velocity. So if an object is moving to the right but slowing down, that means that the acceleration must be pointing to the left to create this new velocity vector after 1 second. And then if that acceleration continues to apply and we connect these tip to tail, you can see that over time the velocity is getting slower. So this is a really important concept. If the acceleration and the velocity point in the same direction, the object is getting faster over time. And if the acceleration and velocity point in the opposite directions, the object is getting slower over time, and vice versa for both. And we can also use that rule in the other direction and say that if the object is slowing, the acceleration definitely points in the opposite direction, and if the object is speeding up, the acceleration definitely points in the same direction as the velocity. This may seem really specific, but the direction that an object is accelerating is going to be one of the most important things that you can identify in high school physics. It's going to come up again and again in future units on forces, and you're going to have to be ready to identify the direction of acceleration. Another common misconception that students have is that they think that positive acceleration means the object is getting faster and negative acceleration means the object is getting slower. But this is not true at all. This is not a correct understanding. The correct understanding is that if the acceleration has the same sign as velocity, again, if it's pointing in the same direction, the object is getting faster. And if the acceleration has the opposite sign as velocity, that means that the object is getting slower over time. I've made a table to demonstrate this where the columns each show a positive starting velocity or a negative starting velocity. And the rows show either a positive acceleration or a negative acceleration, and we can observe how each one changes over time. So these are the starting velocities and the accelerations. And just observing how these are changing over time, you can see that the velocities that are getting faster, that are getting a bigger magnitude, are the ones that have the same sign as acceleration. So just one more time, if the velocity has the same sign as the acceleration, the object is getting faster. This holds true for negative velocities as well. So you can see in the bottom right, there's a negative acceleration, but the object is getting faster and faster and faster in the negative direction. So whether the acceleration is positive or negative by itself tells you nothing about whether the object is speeding up or slowing down. So looking at the other two parts of this table, you can see that when the acceleration and velocity have opposite signs, that's when the object is slowing down, not necessarily when the acceleration itself is positive or negative. There are three ways that an object can accelerate. In high school physics, we never use the word deceleration. We always use the word acceleration to mean any change in velocity, even if the size of the velocity is getting smaller. So even if the object is slowing down, we still call that an acceleration rather than a deceleration. Another situation where an object is accelerating is where it's changing direction, even if it's keeping the same speed. If the magnitude, the size of its velocity is staying the same, but it's changing its direction, that is actually also an example of acceleration. This is the one that confuses students the most because it's not really at all how we use acceleration in the everyday world. In the everyday world, we only use acceleration to mean speeding up and sometimes slowing down, but we never really use it to just mean changing a direction and keeping a constant speed. There are a few different ways I can explain why changing direction is an acceleration, but all of these ways of explaining it comes down to the idea that velocity is a vector. So because a velocity is a vector and has both magnitude and direction, a change in just the direction is still a change in velocity over a certain time, which is an example of acceleration. This velocity that I'm showing now going east is a different vector than this velocity going north. So because here the velocity is changing from east to north, it's a change in velocity even though the size of the velocity is staying the same. So if the direction changes, the velocity technically has changed even though the size hasn't changed. And therefore, because the velocity has changed, it's an example of an acceleration. Another way we can understand this is if we look at the x and y components of the velocity vector, you can see that each individual x and y component is accelerating. The x component is getting slower and the y component is getting faster and faster until the entire vector is just the y component like that. So because those involve two individual accelerations to change the x and y component values, a turn is going to be considered an acceleration. This is a quick video about average versus instantaneous velocity. Average velocity is the total distance or displacement divided by the total time traveled, whereas instantaneous velocity is the speed or velocity at one specific instant in time. This doesn't depend on any movement outside of that instant in time. Just as an example, we can imagine that I want to drive from Washington, D.C. up to Baltimore, and it's going to take a certain amount of time and a certain amount of distance and displacement to travel there. And so I might find that the total distance that I have to drive is 65 kilometers, and it's going to take me about 1 hour of driving. So that means that my average speed is going to be the total distance over the total time, 65 kilometers over 1 hour, which is 65 kilometers per hour. However, as I'm going that average speed, I'm not literally going to be going 65 miles per hour for the entire time. For example, I'm going to be stopped for some portions of the trip. I might be going faster for some portions of the trip. So the speed that I'm going at any one particular instant isn't necessarily the average speed. So there's a difference there. So that's why we use these two words, average versus instantaneous. So in this one moment where I'm stopped, the instantaneous speed would be 0 kilometers per hour. I'm not moving basically. Whereas if I'm on the highway, the instantaneous speed is 80 kilometers per hour, which seems fast, but that's actually around a reasonable 60 miles per hour. And so if I wanted to know what my instantaneous speed was, I would look down at my speedometer, whereas to know what my average speed was, I'd have to add up the total distance that I traveled and divide it by the total time that I traveled. To find the average speed on a position time graph, we just have to find the total distance traveled between the 2 points and divide by the time. And to find the average velocity, we can either find the total displacement over time or actually just draw a line connecting the 2 points and find the slope on the line. So as an example, if the position time graph looks like this, and I want to know the average speed between these 2 points, I need to find the total distance over the total time, and I can see I went up 4 and down 1, so the total distance is 5 meters, and the total time is 10 seconds. So the average speed during that time was 0.5 meters per second. Whereas the velocity, I can actually just draw the straight line because that has a slope of the total displacement over the total time. And the average velocity, taking that slope of that line, is 0.3 meters per second. So that's how we would find the average velocity on that graph. The instantaneous speed and velocity on a typical position time graph is the slope at that exact point. The instantaneous speed is always positive, but the velocity can be positive or negative. So as an example, if you want to know the instantaneous speed at 1 second, you need to know what the slope of the line the point is on is. So here the slope is 2. It's going up 2 over 1. Over here, I can see that the slope is just 0, so that would be the instantaneous speed. And down here, I can see the slope is -1, so the instantaneous velocity would be -1 meters per second. One very common mistake that students make that you need to be very careful not to do is that to find the slope, some students just divide the position by the time like this. Like they would say, oh, the velocity here is 5 over 8. But that's not correct. That's not how you do these problems. The slope is the rise over the run. It's the change in y over the change in x, not just y over x. You're going to have to use the very specific slope that the function has at that point, and I can see here that that slope is still -1, not 5 over 8. There may be times when you have a curved graph, and when you need to find the slope of that, there's no one clear way of doing it. Basically, the best thing to do is to draw an estimation of what the slope looks like there. Like right here, the slope looks to be about that much. And so once you draw that, you can take the slope of that estimation line, and I can see this has about a slope of 3 over 4, and say that that would be the velocity at that one point. Here I can see that the slope would actually just be 0, so at the top of that arc, I would actually say that the slope is just 0. So that's a conclusion. That's what you need to know about average versus instantaneous velocity. This video is about making position time graphs. Position time graphs show an object's position on the y-axis and the time on the x-axis. They're used to show complicated motion on a simple picture. So as an example, this graph represents the position of an object after a certain amount of time has passed. So I'm going to drop an object here, a person, and I'm going to say that this person is starting at a position of 3. So when no time has passed yet, they're at a position of 3. So that would mean that my y-intercept of the graph when time is equal to 0 is going to be a position of 3. I'm now going to allow time to pass, and you're going to observe how that affects the position graph as the person moves. So you can see that they moved from a position of 3 to a position of 6, and it took them 3 seconds. So that means they're moving up 1 unit of position for every second that passes. And you can see that's reflected on the graph. For every 1 second that passes, they're up another 1 unit of position on the graph. For this next part of the graph, they're going to be stopped. And this is what that looks like. You can see they're just staying at the same position as the time passes. Now they'll move like this, and then like this. So I'm going to have you watch a few of these and begin to pick up on any patterns that you notice in how the graph works. Here's another example. So we're just going to observe how the person moves and watch what it does to the position time graph. Okay, now that you've had a few examples of those graphs, I'm going to play an animation and have you try to guess what the graph is going to look like for this specific animation. So I'm going to start this person off at a position of 2 and then run the clock. And I'm going to play this a few times so you have a chance to draw this in your notes and see if you can guess what the position time graph will look like. So we're going to start now. And I can replay that one more time. Okay, here's the answer. This is what it's going to look like. They're starting at a position of 2, so that means that the y-intercept of the graph is going to be at 2. They then move up at 1 meter for every second that passes until they get to a position of 6. Then they stop for 5 seconds, and then they move down at 2 units of position for every second until they're at a position of 0 at 12 seconds. So that's what that graph would look like. We can now begin to pick up on patterns in these graphs. The first one you might have noticed is that the y-intercept of a position time graph is the starting position of the object. This is always true because by definition, the y-intercept is what the y value is doing when the x value is 0. So here, this is what is the position doing when the time is 0, which is the starting position of the object. The slope of the graph is equal to the velocity of the object. The reason why this is the case is because if you look at the rise and the run, I can see that the rise is the change in position, which is the displacement, and the run is the change in time. And because slope is rise over run, I can rewrite that as the displacement over the time, which is equal to the velocity. So this will always be true. The slope of the position time graph is always going to be equal to the velocity because of this definition. So I can look through this graph here and just observe what's happening. For this first section, I can see that this person is moving at 1 meter per second because they have a slope of 4 over 4, a rise of 4 meters and a run of 4 seconds. So their velocity is 1 meter per second. So for every 1 second, they travel exactly 1 meter. In this next section, I can see that this is just a flat line, so the position is not changing at all. So that means that the slope is 0 over 5, which is just 0 meters per second, and that means that their velocity is 0, and you could see also that they weren't moving in that period of time. They were just standing still, so they have a velocity of 0. For this last section, I can see that they're moving down -6 meters in 3 seconds. So that means that their velocity here is -2 meters per second, 6 divided by 3. And I can see here also that when they move down, they're moving down 2 meters for every 1 second that passes. So that's a really important pattern in position time graphs that we can use to help us draw and interpret them. Here's an example problem. What is the starting position of this object and what is the velocity of this object? Well, the starting position is pretty easy. That's just the y-intercept. So that's just going to be 2 meters. The velocity is a little bit more difficult. We just need to take the slope for that. So the run here is 12 seconds. The rise is 3 meters. So the slope is going to be 3 meters divided by 12 seconds, which is equal to 0.25 meters per second. So that would be the velocity of the object on this position time graph. We can also determine the starting position of this object and also determine the velocity at 2 seconds, the velocity at 6 seconds, and the velocity at 10 seconds. The starting position here is 4. That's pretty simple. I'm now going to look up at what's going on at 2 seconds. And I can see here that the line that this is on has a run of 4 seconds and a rise of 2 meters. So that means that the slope at that point is 2 meters over 4 seconds, which is equal to 0.5 meters per second. Over here, this line I can see is perfectly flat, so that means that the slope is just 0. It's 4 seconds long, but it's not going up or down at all, so it's 0 over 4. So the velocity there is 0 meters per second. Finally, at a time of 10, I can see that this line that it's on has a run of 4 and a rise of -6. So I plug those in and I get a velocity of -1.5. So that's how you would find the velocity at different times for an object on a position time graph. This next section is about how to find the distance and displacement on a position time graph. To find the distance, you're just going to add up all the individual distances that this object travels along its path. And to find the displacement, you're just going to compare the beginning and final points that the object is at. So you can see for this object that they're going up 4 meters. And then they're standing still. And then they're going down 6 meters like this. So the total distance here would be 4 plus 0 plus 6. So the total distance would be 10 meters. And the displacement, we just have to compare the beginning and ending points. So they're ending at a position of 0 and they started at a position of 2. So their displacement is just going to be -2 meters specifically. That's how you find the distance and displacement on a position time graph. Here's another example. What is the distance the object traveled after 7 seconds, and what is the displacement it traveled after 7 seconds? So let's compare those two. I can see that the total distance traveled here is going from 1 to 7, so that's a distance of +6. It then stays still, so we don't add any distance there. And then it goes down to 7 seconds, so I can see that it traveled another 5 meters, so the total distance it traveled was 11 meters. The displacement is just the straight line length from where it started to where it stopped. So it started at a position of 1, ended at a position of 2, so the displacement is +1 meters. This is the first part of a 2-part video series on velocity time graphs. We're not going to get into the second part this unit because this unit is about constant velocity. And so this first part is only going to cover graphs of constant velocity on velocity time graphs specifically. So velocity time graphs show an object's velocity on the y-axis and the time on the x-axis. They're used to show complicated motion on a simple picture. So as an example, if this person were to start walking as the time moves, I can see that they have a velocity of 1 and then a velocity of 2 and then a velocity of 0 and then a velocity of -1. And so that's how that would be represented on the graph. I'm going to play that back once more just so you can see it happening again. This person begins to move forward with a velocity of 1 for 3 seconds, and then they have a velocity of 2 for 2 seconds, and then they're stopped with a velocity of 0, and then they have a velocity of -1 for 4 seconds. So that's what the velocity versus time graph of their motion would look like. So something you may have noticed here is that the y-intercept of the velocity time graph is the starting velocity of the object. They started with a velocity of 1 meter per second at a time equals 0, so that's what the y-intercept of a velocity time graph tells you. This next part can confuse students when they first see it, but after some practice, I find that it becomes pretty easy. So the area under the curve of a velocity time graph is the area between the graph's line and the x-axis. And on a velocity time graph specifically, the area under the curve equals the displacement of the object over that time. So I'll show you what I mean by that. This is the area under the curve for the first part of the graph. It's the area between the graph's line and the x-axis specifically, all the area that takes up. And so I can see here that that full area is the velocity times the time, because the area of a rectangle is equal to the base times the height. And because this is the velocity times the time, I remember that velocity times time is equal to displacement. So this area is going to be equal to the displacement of the object. And when I multiply that out, I can see that the area is 3 meters per second because that's the height of the velocity times the 5 seconds of time, which is equal to 15 meters. So that area is equal to 15 meters. So in that time of 5 seconds, the object traveled positive 15 meters. This next area I can see is equal to positive 3 meters. That's pretty easy. It's just 1 meter per second times the 3 seconds that travels for. This next part doesn't have any area under the curve between the line and the x-axis, so it travels 0 meters in that time. In the last part, I can see that this area is actually below the x-axis, so it's still between the line and the x-axis, it's just negative. So this is actually going to be a negative displacement of the object because the velocity is negative. It's going to be negative 2 times 2, which is equal to negative 4 meters. So the total displacement that this object traveled in this time is 15 plus 3 plus 0 minus 4, which is equal to 14 meters. So we can find the displacement of the object from the area under the curve of a velocity time graph. We can try that with our original velocity time graph just to see how that works. So I'm going to have this person move in this way. So I can see here that the area under the curve for that first part is 1 meter per second times 3 seconds, which is equal to positive 3 meters. And I can see that this person did actually move positive 3 meters. Next, they're going to move at 2 meters per second for 2 seconds, and I can see that that area is 2 meters per second times 2 seconds, which is equal to 4 meters. And I can see that they did move another 4 meters there. And altogether, they've moved 7 meters. The next part, they're going to be stopped. And then they're going to go backwards at negative 1 meters per second for 4 seconds. And I can see here that their displacement is going to be negative 1 meters per second times 4 seconds, which is negative 4. And again, I can see they traveled negative 4. And so altogether, their total displacement is 3 plus 4 plus 0 plus negative 4, which is equal to positive 3. So that fits our understanding of the displacement. This is part 2 of the lecture on velocity time graphs. This time we're going to be talking about velocity time graphs of changing velocity. The slope of a velocity time graph gives us the acceleration of the object. Acceleration is the change in velocity over the change in time. So just as a proof of that, you can see that the run of the graph is the time, and the rise of the graph is the change in the velocity. And because slope is rise divided by run, here that's going to be the change in velocity over the time, which, as you know, is equal to the acceleration. So the slope of a velocity time graph is equal to the acceleration of the object. So as an example, we can find the acceleration for each point on this velocity time graph, just finding the slope for each section. This first part has an acceleration of positive 2 meters per second. The second part goes for 3 seconds, but there's no rise, so the acceleration is 0 there, which makes sense because the graph is staying at a constant velocity. So constant means there's no change, so there's no acceleration. For this third part, the run is 4 seconds and the rise is negative 4 meters per second. So this is going to be an acceleration of negative 1 meters per second squared. And lastly, the run of this last part is 2 seconds and the rise is positive 1 meters per second. So the acceleration is 0.5 meters per second. We can still find the area under the curve of a velocity graph with a non-zero slope to find displacement. We just need to use geometry now. So just remembering that the area of a triangle is 1/2 base times height and the area of a rectangle is base times height. This is all you're ever really going to need to find the area under the curve of a velocity time graph with a changing velocity. All you'll have to do is kind of split up the area into different shapes. So this first area, as an example, I can see is a triangle with a base of 3 seconds and a height of 2 meters per second. So that area is going to be 3 meters. This is a rectangle with a base of 6 and a height of 2, so that's going to be 12 meters. This is another rectangle, so that's going to be 6 meters. And this is another triangle with an area of 3 meters. Adding all of these together, I can see that the total displacement in this time is going to be 24 meters. And I can also find information like the average velocity, which is just the total displacement over the total time, which here is going to be positive 2 meters per second. So what I'm trying to say is that you can still get information like this from graphs of changing velocity. You're just going to have to use a little more geometry than before. We can use the properties of velocity time graphs to solve complex problems involving accelerating objects. We're just going to need to use these 3 facts. The y-intercept of the graph is going to be the initial velocity, the slope is the acceleration, and the area under the curve is the displacement. We can now combine all of these facts to solve more complicated problems. So as an example, we can say a runner starts from rest and accelerates at 3 meters per second for 5 seconds. What is their final velocity and what displacement did they cover? So we can solve this using the graph in this way. I know that this runner is starting from rest, so the y-intercept of the velocity time graph is going to be here at an initial velocity of 0. And I know that as I draw this line up, this is going to have a slope that's equal to the acceleration because it's a velocity graph, so the slope is 3 meters per second per second. And I know that this is going to happen for 5 seconds, and I need to know the final velocity and the displacement they traveled. So I know that the slope is the rise over the run, and I can see that the run is the time that has passed, and the rise is actually going to be equal to the final velocity. That height of the rise will be equal to the final velocity, or the change in velocity. So multiplying both sides by the run gets me the run times the slope is equal to the rise. So plugging in what I know, I get that the rise of this graph is going to be 15 meters per second. So because it's starting from 0 meters per second and rises by 15, that is going to be the final velocity of this object. So that's how we can use the graph to find the final velocity, and we can also use it to find the displacement using the area under the curve. So the displacement here is just going to be the area under the curve, which is equal to a triangle's area, 1/2 base times height. Plugging that in, the base is 5 seconds and the height is 15 meters per second. That final answer is going to be 37.5 meters. So that is the displacement of the object. So that's how you can use a velocity time graph to solve more complicated problems involving acceleration. We're just going to do one more example. A car is driving at 30 meters per second when it slows at 4 meters per second until it is at a velocity of 10 meters per second. Once it hits 10 meters per second, it stays at a constant velocity for 7 seconds. What total displacement does it cover? So I know it's starting at 30 meters per second, that's its initial velocity, and then it's going down until it hits 10 meters per second. And then it's going to travel at a constant velocity for 7 seconds. So if it's a constant velocity, there's no acceleration, so there's no slope, so it's just a flat line. And I know in this first part that the slope is going to be -4 meters per second. And so here the rise is going to be going down, and the run is going to be this way. And I can see that the rise here is going to be -20 meters per second. It's dropping from 30 down to 10. So slope is equal to rise divided by run. Multiplying both sides by the run gets me this. And solving for the run by itself, the horizontal length, gets me rise over slope. So when I plug this in, I get 5 seconds as my answer. So that's going to be how long that first part of the graph takes, 5 seconds altogether. So I'm going to put a little 5-second marker right here. And so that means that because there's an additional 7 seconds of travel, the final time there will be 12 seconds. So now we need to know the total displacement. To find the displacement on this graph, I just need the area under the curve. So that's going to be made up of this rectangle and this triangle right here. So solving for both gets me 50 meters on the triangle and 120 meters on the rectangle. So that means that the total displacement is 50 plus 120, which is 170 meters. The total displacement here is 170 meters, and that's how you solve more complicated problems with velocity time graphs. This lecture is going to be about translating position and velocity graphs. Translating a graph means representing the same exact motion on a new type of graph. For this video, we're only going to focus on translating from position time graphs to velocity time graphs, and back from velocity time to position time graphs. So we'll start off by going from position to velocity graphs. To translate from a position time to a velocity time graph, we can use the fact that the slope of the position time graph is equal to the velocity at that time. So because the velocity graph is showing you what the velocity is at that time, and we can find that using the slope of the position time graph, we can translate from one to the other. So we'll show you an example of that using this position time graph here. I'm going to start by breaking this up into sections. I can see that there are different periods of time where the graph has different slopes. So I'm going to draw these vertical lines that just indicate that at that line, the slope is going to change. So the velocity is going to change there as well. These vertical lines don't have any physical meaning beyond this is at a certain time. Okay, I can see that the run here is 4 seconds and the rise is positive 4 meters. So that means that the slope is positive 4 meters over 4 seconds, which is equal to 1 meter per second. And I remember that the slope on a position time graph is equal to the velocity. So that's the object's velocity for the first 4 seconds, positive 1 meters per second. For the next portion, I can see that it's just a perfectly flat line, which means it has a slope of 0 and therefore a velocity of 0. In the next section, I can see that I have a run of 2 seconds and a rise of negative 4 meters. So that means that the velocity is negative 4 meters over 2 seconds, which is negative 2 meters per second. And in the last part, I can see I have a run of 2 seconds and a rise of 6, like this. That line keeps going, but as long as we can get some slope from the line, that's the same slope for the rest of the line. So it's going over 2 and up 6, so that means it's 6 meters over 2 seconds, which is equal to 3 meters per second. So within each section, the velocity is staying constant. The slopes aren't getting steeper or shallower within each section of time. They only change when you go from one section to the next. So that means that on the velocity graph, we're just going to record horizontal flat lines that show that the velocity is staying the same for each of those sections. So in the first section of the graph, I know that the velocity is positive 1, so we'll just record that. It's staying at positive 1 for 4 seconds. In the second part of the graph, the velocity is just 0. In the third part of the graph, the velocity is negative 2 meters per second, and in the fourth part, it's positive 3. So that's what the velocity time graph would look like for that position graph. We're now going to go into translating from velocity time to position time graphs. There are two different ways we can translate from a velocity time to a position time graph. For both, we can start from any position on the PT graph because the VT graph tells us nothing about the starting position. This is really important. When you're translating from velocity to position, the velocity graph tells you nothing about what position you start at, so you can choose the position yourself. So we can either use the fact that the velocity is equal to the slope of the position graph and then draw lines on the position time graph with the correct slopes, or we can use the fact that the area under the curve of the velocity time graph is equal to the displacement in that time. I'm going to give you an example of using each one. I'm going to start with the first one using just the fact that the slope is equal to the velocity. And before I start, I'm going to draw those vertical lines that separate different parts of the graph by the time that they're happening at, just because I have these different sections with different velocities. Okay, so I can see that I'm going to have a velocity of 2 for 3 seconds. So that means that on the position graph, my slope is going to be 2 for 3 seconds. So I'm going to draw 2 up, 1 over, and then keep drawing that line until I have this. So I can see that this is a line with a slope of 2 that lasts for 3 seconds. Next, I can see that I'm going to have a velocity of negative 1 for 5 seconds. So I'm just going to go down 1, just going down 1 and over 1 like that for 5 seconds. After, I can see I have a slope of 0, so that means the velocity is 0, so the position is not changing at all here. So that's just a flat line there. And finally, I have a velocity of positive 3, so that means that the slope is going to be positive 3 over 1, and it'll look like this. So that's one way of translating from a velocity graph to a position graph using the slope of the line of the position graph. The other way is to use the area under the curve, which is what we'll do now. Okay, so I remember that the area under the curve of a velocity graph is equal to the change in position. So I just need to find the area for each section and then record that as the change in position on the position graph. And again, before I do that, I'm just going to section this off into the specific velocities that it has. Okay, now I'm going to go through and figure out what the area under the curve is for each section. And just as a reminder, the area under the curve is the area between the line and the x-axis, like this. So I can see that this has an area of 2 times 3, 2 meters per second times 3 seconds, which is equal to positive 6 meters. Because when I multiply meters per second times second, it just comes out to be meters. So that means that the change in position here is going to be positive 6. Over those 3 seconds, the position is going to be added to by 6 meters. So if I start at 0 and change by positive 6 in 3 seconds like this, this is what that line is going to look like. So that's the first part of my graph. In the second part, I can see that I have this negative area. It's below the x-axis, so we consider that to be negative. And when I find that area, I find that it's equal to -5, just -1 meters per second times 5 seconds. So the change in position here is going to be -5. So if it's at 6 and it goes down by -5, this is what it's going to look like, down by -5 in those 5 seconds. So the final position will be here, and this is what that line will look like. Okay, this next section is pretty simple. I can see that there's no area at all, so that means that the area is 0 meters. So in those 2 seconds, the position is going to change by 0 meters. So it's going to be at the same position as it was before. And lastly, I can see that this last area here is also +6 meters. And this time it covers that in 2 seconds. So that means that it's going to go up 6 in 2 seconds, and that is what that line is going to look like. So that's how you translate from velocity time graphs back to position time graphs. This video is about acceleration time graphs. You may have guessed by now that acceleration time graphs show an object's acceleration on the y-axis and the time on the x-axis. They're used to show complicated motion on a simple picture. For the next few units, we'll only be looking at situations with constant acceleration. So all of our acceleration graphs will be horizontal lines. It's pretty rare in physics to have non-constant acceleration. There's really only 1 or 2 places in the whole year where non-constant acceleration shows up. So for the foreseeable future, all the acceleration time graphs that we deal with will just be horizontal lines. So as an example, we can imagine this object that's accelerating at 3 meters per second for, let's say, 3 seconds. So on its speedometer, because it accelerated at 3 meters per second for 3 seconds, its final velocity at the end of that is going to be 9 meters per second. We can then imagine it decelerating at 2 meters per second for 2 seconds. I'm just kind of making up numbers here. Then at 1 meter per second for 3 seconds. And then at -1 meter per second for 4 seconds, like that. You may have guessed that an important property of acceleration time graphs is going to be the area under the curve. Again, that area is the area between the line of the graph and the x-axis. On acceleration time graphs, the area under the curve is going to be the change in velocity of the object over the time that has passed. So as an example, on this graph that I'm looking at here, this area is a rectangle and the height is acceleration and the base is the time. So the area is going to be the acceleration times the time, which if you plug that into the acceleration equation, you'll see is the change in velocity. Plugging this in, here that change in velocity is +15 meters per second. Plugging this in over here, I can see that this next area has a height of 1 and a base of 3, so that's going to be +3 meters per second. That next acceleration is just on the x-axis, so it doesn't have any change in velocity. And that makes sense because if the acceleration is staying at 0 and acceleration is a change in velocity over time, that means that there's no change in velocity over time. I can see that that last area is negative between the x-axis and the line of the graph, so that means that the area itself is going to be negative. The change in velocity will be -4 meters per second. So I can see that altogether, the total change in velocity on this graph is going to be +14 meters per second when I add these together. I'm going to go back to my example just to give you an intuition about the area under the curve of the acceleration time graph. So for the first 3 seconds, it's accelerating at 3 meters per second. And I can see that it went from 0 meters per second to 9 meters per second on the speedometer. And over here, I can see that this area is +9 meters per second. And that makes sense. It went from 0 to 9 meters per second, so the change is +9 meters per second. In this next part of the graph, the acceleration is -2 meters per second. So if I look at that area, I can see that that's -4 meters per second, and I can see that my velocity did change by -4 meters per second in that time. Next, it has an acceleration of +1 for 3 seconds, and again, I can see that the area is +3 meters per second, and it changed by +3 meters per second in that time. And finally, this is -1 meter per second for 4 seconds. and the velocity changed by the area, which is -4 meters per second, so it changed by -4 meters per second on my speedometer as well. We can translate from an acceleration time to a velocity time graph and vice versa. To translate from a velocity time to an acceleration time graph, we can use the fact that the slope on the velocity time graph is equal to the acceleration at that time. So I'm just going to section this off and find the slope at each point and call that the acceleration. In this first part, I can see that the slope is just +1 meter per second per second. In the second part, that's a flat line, so the slope there is going to be 0. In the third part of the graph, I can see that this is the run, this is the rise, so the slope is going to be -2 meters per second per second. And in the last part, this is the run, this is the rise, so the acceleration is +3 meters per second per second. I'm now going to draw all those numbers on my acceleration time graph. So the first part is a constant acceleration of 1, the second part is a constant acceleration of 0, the third is a constant acceleration of -2, and the last part is a constant acceleration of +3. So that's what the acceleration time graph would look like for that velocity time graph. There are two ways we can translate from an acceleration time to a velocity time graph. For both, we can start from any velocity on the velocity time graph because the acceleration time graph tells us nothing about the start velocity. So the first way I'm going to show you, this first example, is to use the fact that the acceleration is equal to the slope of the velocity graph. So we can just draw lines on the velocity time graph with the correct slopes based on the acceleration in each section of the acceleration time graph. So we can see that that first section over here is going to have an acceleration of 2, so that means that the slope of the velocity graph is going to be +2. So just drawing that line up 2 at a time, like this, for 3 seconds, gets me this line. In the second part, the acceleration is -1, so that means that the slope is going to be -1 for 5 seconds. For the third part, the acceleration is 0, so the slope is 0. And for the fourth part, the acceleration is +3, so that means that the slope is +3 for 2 seconds like that. So that's one method we can use. The other method that we can use is finding the area under the curve and knowing that that's how much the velocity changes in that time. So I'm going to section this off again. And I'm going to find the area under the curve for each part of the acceleration time graph. So this first area is +6 meters per second, pretending here that the velocity starts at 0. I know that after 3 seconds, it's going to be rising by 6. So the next point on the graph will be over here. I can draw that connecting line, and that's what the first part of my graph looks like. The second part has an area under the curve of -5 meters per second. So I know I'm going to be going down 5 in that amount of time. So that's where the next point on my graph will appear. This next part has an acceleration of 0, so that means the slope is 0, so it's really just staying at the same velocity. In this last part, the area under the curve is +6 in 2 seconds, so that means that the velocity is going to change by +6 meters per second in 2 seconds. So that's the other way of translating from acceleration time graphs back to velocity time graphs. Now that you know how to translate between all 3 types of motion graphs, position, velocity, and acceleration, this video is going to give you a bunch of examples of how to translate between all 3 types of graphs at once, from position, velocity, acceleration, and back down from acceleration to velocity to position. As you know from previous lectures, we can make multiple different graphs of the same motion using position, velocity, and acceleration graphs. For example, this person here, we can observe their motion and create a position time, velocity time, and acceleration time graph. So I can see that this person started off fast and then slowed down, and so I made this position time graph of what their position looks like over time. And we can also make a graph of their velocity over time. It starts large and goes down to 0, and we can also make a graph of their acceleration over time. Because they're slowing down, the acceleration is occurring in the opposite direction of their velocity, so it's negative. So all 3 of these graphs represent the exact same motion, just a different aspect of that motion, the position, the velocity, or the acceleration. So in this lecture specifically, I'm going to show you how, using information from one graph, you can understand what the other 2 graphs will look like. So as you know, the 3 graphs have this relationship between themselves. The velocity is the slope of a position graph, and the acceleration is the slope of a velocity graph. and the area under the curve of an acceleration graph is the change in velocity, and the area under the curve of a velocity graph is the change in position. We're going to be using these rules specifically to translate between a bunch of examples to show you how they work. And I found that a lot of students struggle with when slope is larger or smaller or positive or negative. So I've left this chart above my head to remind you of when slopes are which value. So a very steep upward slope is a more positive slope. A more shallow upward slope is a less positive slope. A perfectly flat line is a zero slope. And then a slightly downward slope is a slightly negative slope. And a steeper downward slope is a slightly more negative slope. That's going to be really important in translating these graphs, so make sure you have that committed to memory. Okay, in this first part of the video, I'm only going to focus on translating between position and velocity graphs and back. So starting off with this steep straight line, I can see that this would be an example of a very positive constant velocity. So the velocity graph for this position graph would look like this. It's staying at the same velocity. It's a flat line because the slope of the position graph is staying constant. So because velocity is the slope of a position graph, a constant slope means a constant velocity. If I make this slightly less steep green line, I can see I have a slightly less large velocity because the slope is less large on the position time graph. This pink line that I just drew is perfectly flat, so that has a slope of 0 and it's constant, so that means the velocity is also constant and 0. And then this is a slightly negative slope and a more negative slope for a slightly and more negative velocity. So this graph you probably know how to translate as well. This is going to start off with a very positive velocity because it has a very positive slope. And then the second part will have a velocity of 0 because it's a flat line. And the third part will have a slightly negative velocity. It's closer to 0 than that first line though, because that last line is more shallow. And as a reminder, if you need help translating, you can always draw these vertical lines. These just show different time intervals. They don't really mean anything physical beyond that. So if you're having trouble seeing where the graph changes from one to the next, drawing those lines between the graph can definitely help. Here's an example where the position time graph has a constant negative slope, so therefore it has a constant and negative velocity as well. And here on the second part, it has a constant positive slope, so that means that the velocity is going to jump to being constant and positive rather than constant and negative. Here are a few more examples. I'm running through this quickly just to make sure that you get the idea of how to translate them before we move on. Okay, this is a new concept that we haven't seen before. This is a curved position time graph, and we want to understand how to convert it into a velocity time graph. So the issue with a curved graph is that the slope is constantly changing. That's the definition of a curved line. It's not straight, so it has different slopes at different points. So that means that the velocity is constantly changing also. So we need some way of understanding what the velocity is doing at different times. So my personal favorite trick for translating any of these graphs is to draw what are called tangent lines next to the graph that I'm translating if I'm trying to understand what the slope is doing. So a tangent line is a small, perfectly straight line that imitates what the slope of the graph is doing at that exact point where it's drawn. So if I were to draw tangent lines along this position time graph, they would look something like this. You can see that each one is imitating what the slope is doing at that exact point. So this is going to help us understand what the velocity is doing for every second that passes. So because the velocity is the slope of the position time graph, I can just look at these tangent lines to understand what the velocity is at different points in time. I can see, for example, that that first slope is 0, so that means that the velocity is also going to be 0 to start off. And then over time, the velocity is going from 0 to a little positive to more positive to very positive. That's what the slope is doing. So my velocity graph is going to do that as well. At a constant rate, it's going to go from 0 to a little positive to more positive to very positive. So that's what the velocity time graph would look like for this position time graph. It's going to be rare that you see a curved velocity time graph in this course. That comes up a little bit in the projectile motion unit, but besides that, it's relatively rare. And so for now, you can just assume that the velocity is increasing in a constant linear rate. So that's how you would translate that position time graph into a velocity time graph. We can try the same thing with this one now. Again, I'm not really going to think about this too much. I'm just going to draw those tangent lines next to the line of my graph and try to figure out what the slope is doing at each point. So I'm drawing those tangent lines. And looking at these tangent lines, I can see that that very first slope up top is very, very negative. It's going down very quickly. So that means that my velocity is going to start off very, very negative. And I can see that the final tangent line is 0, and all the tangent lines in between are becoming less and less negative. They're all negative, but they're getting closer and closer to 0 at the end. So that means that the velocity is going to start very negative and become less negative until it hits a velocity of 0 at the end. So that's what this velocity time graph would look like. This is another example. Again, I'm going to start by drawing those tangent lines. Okay, so here I can see that the velocity starts very positive. The position time graph has a very positive slope at the beginning. It then goes to 0 at the halfway point because it's a flat line at the halfway point. And then after, the velocity is going to be a little negative and then more negative and then more negative. So it's just going to keep going through 0 down into the negative. So that's what the velocity time graph would look like for this position time graph. We can now go backwards and translate back from a velocity graph to a position graph. So to start off, I'm going to imagine that we have this constant positive velocity here. I'm now going to draw those tangent lines on the position graph because I remember that the velocity tells me the slope of the position graph. So I know that because the velocity is constant and positive, the slope on the position time graph is also going to be constant and positive. Also remember that the velocity time graph tells you nothing about the starting position of the object. So I'm just going to imagine that it starts in the negative just so that I have enough room to go up. So I have these constant positive slopes that I'm adding. And so the position graph could look something like this when I draw it out. It could have also started from a different position. It could have started from the 0 point or up higher. It doesn't really matter. There are multiple correct answers here because the velocity time graph tells me nothing about where the position graph starts. I can see that this is another velocity time graph, but this time it's a lower velocity. So that means that the slopes are just going to be lower. They're going to be shallower like this. And again, I can start this from wherever I want. So I've decided that the position time graph looks like this in this case. Just a more shallow slope, still going up because the velocity is positive. This is at a velocity of 0, so that just means that the slope of the position time graph is going to be 0 the whole time. This velocity is negative, so as a result, the slope of the position graph is negative, and this is a very negative velocity, which means a very negative position time graph slope. Okay, so now we're getting into something new. We have a changing velocity, and we want to translate that into a position time graph. So I can look down and see what the velocity is doing at different times. So it's starting at a velocity of 0. So that means that the slope of the position time graph is also going to start at a slope of 0. So it's starting flat. And again, I can start the position time graph wherever I would like. The velocity graph tells me nothing about the starting position. So I'm going to start this a little high because I know we're going to be going down over time. So the slope starts at 0 and then progressively becomes more negative because the velocity is becoming more and more negative like this. So if I draw this out, this is what the position time graph would look like. It's a curve because the slope is constantly changing because the velocity is constantly changing, and it's going from a slope of 0 where it's flat to becoming more and more negative, going more and more in the downward direction. Okay, this graph is surprisingly complicated. This is a velocity that starts negative, goes to 0, and then becomes positive. So we can draw what the position time graph would look like. So this is going to start with a very negative slope because the velocity is very negative. And then I know the slopes are becoming less and less negative over time. They're going to a slope of 0 in the center. So I'm going to draw that out. They're becoming less and less negative over time. And then right here, it hits a slope of 0. And afterwards, the slopes are slowly beginning to get more and more positive. So the second part will look like this. So this is going to be this interesting curve here. It's going to curve down and then back up. It's very difficult to just eyeball these and guess what they will be. You need to pay very close attention to the slope and what the velocity is telling you about the slope. You can also use the area under the curve if you want, where each individual area under the curve tells you how much the object's position changes over time. So it basically also tells you the value of the slope. So here you can see that the areas under the curve can tell you the values of the slope. They're either very negative, less negative, 0, positive, or more positive like this. Okay, so now that we've translated from position to velocity and back from velocity to position, we can begin to translate from velocity graphs to acceleration graphs. Just a reminder, on a velocity time graph, slope is equal to acceleration. Like before, I'm just going to draw out these patterns super quick to show you how each individual velocity graph would be represented on an acceleration graph with a constantly changing velocity. Pretty straightforward. The acceleration is just the slope of the velocity graph. Again, the acceleration just shows you the value of the slope at that point. It's never really going to get more complicated than this for velocity time graphs because, again, we almost never deal with a curved velocity graph, and when we do, we'll use some special rules for it. I'm just going to run you through a few more examples really fast just to show you what a few more of these would look like, but I think you probably get the idea by now. We can also go backwards from an acceleration graph to a velocity graph. So here, this acceleration is constant and positive, so that means that the slope of the velocity graph will also be constant and positive. Here, the acceleration is 0, so that means that the slope of the velocity graph is also 0. Here, the acceleration is constant and negative, so that means that the velocity's slope is constant and negative. Here, it changes from negative to positive, so that means that the slope of the velocity graph will change from negative to positive. And the acceleration time graph tells you nothing about the starting velocity of the object, so you can start the velocities at any point you would like. You can also use the area under the curve of an acceleration graph to tell you what the change in velocity will be over that time. So now that you know these rules, I'm going to give you a few examples of translating between all three types of graphs, from position to velocity to acceleration and back. I'll start with this position graph. I can see that this has a constant positive slope, so I know that velocity is the slope of a position graph, so that means that the velocity is going to be constant and positive. And now translating from a velocity to an acceleration graph, I know that the slope of the velocity graph is the acceleration, and because the slope of that velocity graph is 0 over the whole time, that means that the acceleration is also going to be 0 for the whole time. So that is the exact same motion represented on all three types of graphs. So again, translating graphs means to express the same motion using a different graph. Just like translating a language means expressing the same idea in a different language. We can now translate this curved position time graph. It's curving up, so I can see it starts with a slope of 0 and the slope gets bigger and bigger and bigger over time. And so that means the velocity is going to start at 0 and get more and more positive over time. And now to translate from velocity to acceleration, I can look at the slope of the velocity graph and see this is constant and positive. So that means that the acceleration is also going to be constant and positive. So the acceleration time graph will look like this. Here's another example. This time we're given a velocity graph and asked to translate to a position graph and an acceleration graph. So I'll start with position. So I can see that the velocity is starting very positive and over time becoming less positive until it hits 0. And then it's becoming more and more negative. So that's what my position time graph will look like. And my acceleration time graph shows me the slope of the velocity time graph, and that slope is constant and negative, so the acceleration is also going to be constant and negative. Here's one last example of going from an acceleration graph to the other two. So I can see I have a positive acceleration and then a negative acceleration. So that means that my velocity is going to start with a constant and positive slope, and in the second half it will have a constant and negative slope like this. And again, I decide where the starting velocity is. Here I decided it's around 0. And now going from velocity to position, I can see here that the position graph is going to start with a slope of 0 because the velocity is starting at 0. I kind of arbitrarily decided that. And then it's becoming more positive over time until it's very positive at that central point. And then after that, it's going to become less positive until it hits a velocity of 0 again. So this slope is going to become less positive, and it's still positive. It's still going up. It's just going up at a less steep slope than it was before. So it's going to keep going up at a slower and slower rate until it hits 0 again. So this is what the position time graph of that object represented in those other two graphs would look like. Okay, that was everything. That is how you translate between all three types of physics graphs. This lecture is about the kinematic equations, which are some of the most important and central equations in all of physics. They come up again and again in many different topics. Before we go in, I'm going to start with the definition of kinematics itself. So kinematics is the branch of physics concerned with the motion of objects without reference to the forces which cause the motion. What this means in everyday language is that kinematics is the way that we predict different parts of the motion of an object only using other parts of the motion. We don't need to know anything about what type of object it is or what forces are acting on it to predict its motion. We just need those other parts. So the main idea is that any object in the universe, no matter what it is, if it's an asteroid in outer space, if it's a toy here on Earth, if it's anything in between those things, if we can understand just a few small parts of its motion, we'll be able to predict the rest of its motion without any other information about what it's doing or what forces are acting on it. So these are the equations and the kinematic variables. You can see that there are 5 variables that the kinematic equations connect: displacement, initial velocity, final velocity, acceleration, and time. I've written the variables for each and the unit that we use to measure each in the boxes up here. If you get any values that are given in different units than what's on the list above, it's best to convert the units back to the units shown here. That's usually the easiest way of solving the problem, to convert everything back to these base units specifically. The 4 kinematic equations are written above my head. Each kinematic equation connects 4 of the 5 kinematic variables. So that means that you're going to have to select different equations to use based on the variables that you have and the variable that you're looking for. We're going to talk about that a lot in this video. There are 3 steps to solving a kinematics problem. I'm going to have you copy these steps down. I'm not going to read through all of them right now. I'm just going to emphasize one really important thing in step 2. This is a really central idea in kinematics. Kinematic equations can only be used if the acceleration is constant over the motion they are predicting. Nothing else about the object being analyzed has to be constant. The position doesn't have to be constant, the velocity doesn't have to be constant, the velocity can change from positive to negative, the position can change from positive to negative. The only rule that will prevent you from using a kinematics equation is if the acceleration is not staying constant. That's the only time when you cannot use a kinematics equation. And even then, there are often solutions available. If the object accelerates at different rates at different times, you just have to split the problem up into multiple parts where each part has a constant acceleration. I'll show you how to do that a little later in this video. So I'm going to run you through these 3 steps and show you how to solve them. This is example number 1, the first kinematic problem. A dog is running and starts to get faster at 2 meters per second for 3 seconds. If the dog covers 20 meters over this time, what velocity did it start with? Okay, so step number 1 is to define one direction as being positive and the other as being negative, and it doesn't matter which direction we choose as long as we keep that consistent through each variable in the problem. So I'm going to consider the direction of the dog's motion as being positive, and I'm going to kind of arbitrarily define that as being to the right. So the dog is moving to the right and positive. I just kind of arbitrarily chose that. Step number 2 is to check and see if you have more than one acceleration in your problem, and if you do, you're going to have to split the problem up into multiple sections. And here I can see that I don't have more than one acceleration, it's just that 2 meters per second. So I'm going to skip step 2 because I don't have more than one acceleration. Step number 3 is to use a Suvat table and the guess method to identify the correct equation and solve the problem. If you have 3 kinematics variables, you can solve for the missing variable. This is what a Suvat table looks like. Suvat just stands for every variable in the kinematics equations: displacement, initial velocity, final velocity, acceleration, and time. So I make this table to start filling in any data that I'm given from the problem. And the rule is that if you have at least 3 kinematic variables, you can always use them to solve for the other 2. So I'm going to start to fill this in and see if I can solve for the missing kinematic variable. So I can see right away that my acceleration is 2 meters per second. I'm going to consider that to be positive because the acceleration must be happening in the same direction as the dog's velocity because the dog's getting faster and faster and faster. So because that acceleration is happening in that same positive direction, I'm also going to consider it to be positive. Just a reminder, I'm not calling this positive just because the dog is getting faster. It's possible to have a negative acceleration and a negative velocity, which means that you would be getting faster in the negative direction. The reason why I know the acceleration is positive here is because I decided to call the direction of the dog's velocity positive, and if the dog is getting faster, that tells me the acceleration and velocity point in the same direction, and because velocity is positive, acceleration will be positive. So it's going to move that way for 3 seconds. And the displacement the dog covers is going to be 20, and I know that's positive 20 because if it's moving in the positive direction, it's going to cover a positive displacement. And I want to know what velocity it started with, so I'm looking for u. I'm now going to use the steps of the guess method to finish this work. The SUVAT table takes the place of the givens and the unknowns in the guess method. I've already filled in my givens and my unknowns, so now I just need to identify the equation and then solve and substitute. So to find an equation, I'm looking for a kinematics equation that has S, U, A, and T, the things that I have, the thing that I need, and nothing else. Looking at my equations here, I can see the only one that has S, U, A, T, and no V is the second equation right here. So I'm going to take that second equation and put it in my equation section right there. So that's the equation that I'm going to use. I'm now going to solve the equation for u. So just writing this out, I can see that u by itself is going to be equal to s over t minus 1/2 a times t. Finally, I'm going to substitute, plugging in my values, solving for u. This gets me 3.7 meters per second. So 3.7 meters per second is my answer to the problem. It's the initial velocity of the dog. So if you want to move 20 meters while accelerating at 2 meters per second for 3 seconds, your starting velocity absolutely has to be exactly 3.7 meters per second. So the thing that physicists like about the kinematics equations is that this doesn't just apply to this one situation. This holds true for literally any moving object in the universe. To make these other things work, to give you that displacement, that acceleration, and that time, you need to also have that exact starting velocity. So it doesn't matter whether we're talking about a dog or a car or a planet or an asteroid or literally anything, the kinematics equations will always apply and give us that same answer. Going on to example number 2, a ball is rolling up a hill at 10 meters per second, but gravity is causing it to slow at a rate of 1.5 meters per second squared. The ball is accelerated by gravity until it is moving at 5 meters per second down the hill. How much time did this take? Diving into step number 1, we need to identify one direction as positive and the other as negative. So this time we do have two directions. We have up the hill and down the hill. So I'm going to consider up the hill to be positive and down the hill to be negative. And again, if you chose opposite signs for the direction, you would still get the same answer at the end. So in step number 2, kinematics equations can only be used if the acceleration is constant over the motion they are predicting. And here I can see that I still have just one constant acceleration. This ball is just being constantly accelerated by gravity at this rate of 1.5 meters per second per second. So I'm going to skip step number 2 because that doesn't apply here either. So in step number 3, we're going to be filling in that SUVAT table, identifying an equation, and solving and substituting. So I'm going to go through. I can see that the starting velocity is up the hill at 10 meters per second. So I'm considering up the hill to be positive, so I record that number as positive. The acceleration is slowing it down, and again, negative acceleration doesn't necessarily mean that the object is slowing. The reason why I chose acceleration to be negative here is only that if it's slowing down and it has a positive velocity, acceleration must point in the opposite direction as the velocity, because slowing means the acceleration is working against the velocity to make it slower. So acceleration must point in the opposite direction as the velocity, so if the velocity starts positive, the acceleration is going to be negative. So that's why I know the acceleration is negative, not necessarily because it is slowing, but because it is slowing and the starting velocity is positive. We know that this acceleration continues to apply until the ball is moving at 5 meters per second down the hill. So down the hill I've defined as negative, so I have to record that 5 meters per second as negative 5 meters per second like this. And we want to know how much time this took. So just to clarify, what's happening here is that this ball is going up the hill, slowing to a stop with a negative acceleration, and then the negative acceleration continues to apply after the velocity is at 0 when it's stopped, and it begins to make it faster and faster in the negative direction. So that's another reason why the final velocity is negative here. So by the time the final velocity comes around, the acceleration, that negative acceleration, is causing it to move faster and faster and faster down the hill, because the negative acceleration is adding to the negative velocity to make it more large in the negative direction. So I need to identify my equation and then solve. Looking at my equations here, the only one that connects u, v, a, t, and doesn't have s in it is the first equation right here. So that is going to be my equation. And now I need to solve for t. And this is what t is going to be. And now I just need to substitute. And when I solve this out, I'm going to get 10 seconds. You'll notice that the units perfectly cancel out 2 seconds. So that means this is going to take exactly 10 seconds for the ball to change its velocity from positive 10 to negative 5. This is the last example, number 3. A car is accelerating from rest at 5 meters per second. It does this for 10 seconds before it stops accelerating and drives at a constant velocity for 4 seconds. It then slows to a stop at a constant acceleration in 6 seconds. What total displacement did it cover? So here, I can see that we actually do have 3 different accelerations. There's an acceleration where it's speeding up, there's an acceleration where it has a constant speed, and there's an acceleration when it's slowing down. So I have to split this up into 3 different kinematics problems. So this is step number 2 actually being used. You have to split up the problem into different sections where each section has one constant acceleration. So instead of writing out the steps and the equations, I'm just going to show you how you would solve each part of this problem. I can see that the acceleration in the first part when it's speeding up is 5 meters per second. And in the second part, it's just moving at a constant velocity, which means that the acceleration is 0. The velocity isn't getting bigger or smaller in that time. There's 0 change in velocity if there's a constant velocity. And when it's speeding up, it's taking 10 seconds altogether, and it's at a constant velocity for 4 seconds. And this last period of motion is going to be 6 seconds. It says that it starts from rest, so in the very first part of its motion, its starting velocity is 0. And the final velocity at the very end of its motion is also going to be 0. It's slowing to a stop in those last 6 seconds. My rule is that if I have at least 3 kinematic variables, I can always use them to solve for a 4th kinematic variable. So in that first section where they're speeding up, I can plug those 3 into a kinematics equation. In this case, it's actually going to be v equals u plus at to solve for the missing variable. So I can use that equation to find v is equal to 50 meters per second. I'm going to skip the math there just because I want to show you the overall structure of this problem. And because this is the final velocity of its speeding up phase, if you think about it, that's going to be the starting velocity of its constant velocity phase. So it's going to start the period where it has constant velocity with the same velocity that it ended with when it was speeding up, because it's speeding up and then moving at a constant velocity. So the final velocity speeding up is the starting velocity when it's constant. So that's going to be 50 meters per second. And using kinematics, I can see that this is also going to be 50 meters per second, the final velocity. And because that's the final velocity in the constant velocity phase, that's going to be equal to the starting velocity when it begins to slow down. So I'm really just piecing together whatever information I can, and as soon as I fill a SUVAT table with at least 3 variables, I can use those 3 to solve for other variables on the table. So in that first situation, I can use my SUVAT variables to find the total displacement is 250 meters. Plugging in my variables in the second section gets me a displacement of 200 meters. And now that I have all three in the last section too, I can solve that too and find that that displacement is 150 meters. So that means the total displacement is going to be the three displacements added together, which is going to be 600 meters. So that's how you would solve a kinematics problem involving multiple different accelerations. You split the problem into multiple parts, make connections between each part. In this case, the final velocity of one is equal to the initial velocity of the next. And anytime you get at least three kinematics variables, you can always use those three to solve for a fourth in the same table. Now that you know about what the kinematic equations are and what they do, I want to take one video lecture to explain why they look the way they do. There are two ways you can prove kinematic equations. One is with geometry and the other is with calculus. I'm going to stick with geometry for now just because it's a little more accessible. I'm going to be proving all four equations starting with number one and going down the list. These proofs are going to be based on the geometry of a velocity time graph, and we know some properties of that geometry and what that geometry physically means. I'm just going to use what we know to prove the kinematic equations. I'm going to draw an example line on this velocity time graph, and we don't need to know the exact numbers to know what different parts of this graph mean. For example, we know that the starting place of the velocity time graph, the y-intercept of the graph, is going to be the starting velocity, which in the kinematics equations we call u. So that length from 0 up to that point is equivalent to the starting velocity. And the last point on the graph is equal to the final velocity of the object, v. So these are two things that we know about the graph. I'm going to draw one more line and prove what this last line is equal to in just a moment. This is going to be important for visualizing why this first kinematics equation works in the way that it does. So this line is just the total rise of the graph, just from where it starts to where it ends, not from the 0 point. So it's just from where this graph begins to where it ends. And you'll notice that u plus that additional part, which I've labeled in blue with a question mark, is equal to v. So I'm going to write this equation up here. That purple part is equal to the orange plus the blue, or v is equal to u plus this additional section. So I'm just going to prove to you now what this additional section is equal to. Now, I know that slope, the slope of the velocity time graph, is equal to the rise over the run. And I also know that the run of this graph is the total time that this object has been moving for, because time is the x-axis, and that horizontal line is how much of the x-axis has been covered. And I also know that the slope of a velocity graph is equal to acceleration. So I'm going to replace these two things in my equation down here. So I know that the slope is a, and the run is time, or t. So if I multiply both sides of this equation by t and cancel this out, I find that a times t is equal to that rise. So acceleration times time is equal to that blue line. So I can replace that blue line with acceleration times time, and you can see I've just proved my first kinematics equation. That geometry is why that first kinematics equation works the way that it does. I'm now going to prove the second equation. I know that the area under the curve of a velocity graph is equal to the displacement of the object. So I just need to come up with an equation for the area of this graph, and I'm going to be able to prove that second equation for displacement. I'm going to take that area you can see in the top right corner and split it into two parts because this is kind of a complicated shape, but I can split it into a right triangle and a rectangle. So I'm going to do that. So I'm going to say that the total displacement of this object is the area under the curve, which is just going to be that triangle plus that rectangle. And I know that the area of a rectangle is base times height, and I can see that the height of this rectangle is equal to the initial starting velocity of the object, and the base is equal to the time that the object is in motion for. So therefore, the area of the rectangle is equal to the time times that starting velocity, base times height. So I'm just going to set that equal up there, and that'll form part of my equation. For the area of the triangle, I know that the base is time, and I know from my previous problem that that height is equal to acceleration times time. And I know that the area of a triangle is 1/2 base times height, so I'm just going to plug these into that equation. So the area of the triangle is 1/2 times time times a times time. And when I multiply all that together, I get 1/2 times a times time squared. So that's the area of the right triangle. And when I add these things together in the equation, it comes out to say this. The total displacement of this object is equal to the starting velocity times time plus half the acceleration times time squared, which is actually our second kinematics equation right there. So I've just proved another kinematics equation. The third equation is going to require some knowledge of the area of a trapezoid. There's an equation for the area of a trapezoid which says that it's equal to the length of base 1 of the shape plus the length of base 2 of the shape, all times the height and then divided by 2. So I'm just going to plug that in here. I'm going to say that these are the two bases of the shape, the two kind of flat parallel parts of the shape. And so I'm basically just flipping this on its side just to show you how this equation works. So time here is going to be the bottom, which if I flip it on its side is going to be the height of the trapezoid. So I just plug this into my equation, and when I plug this in, I get the length of the base is u plus the length of the other base is v, so u plus v times height, which is just time over 2, and that's equal to the area, which I know is equal to the displacement of the object, so the displacement is equal to u plus v over 2 times t, which is that third equation. And you can see that this equation would not work if the slope was not constant. If I had a shape like this is not a trapezoid. This is a more complicated shape. So this is an explanation of why even if you don't have acceleration in the equation itself, the acceleration still has to be constant for this equation to apply, because this only works with trapezoids, and if the slope is not constant, then the shape is not a trapezoid. And because the slope is equal to the acceleration itself has to be constant here. So this is my third equation. I'm going to check that off. Okay, this last proof is going to be a little ugly. I can't prove this one with geometry, but I can prove it using two of the equations that we already have. So just watch closely. If I subtract the initial velocity from both sides of this top equation up here, I get v minus u equals a times t. And if I divide out a from both sides, I find that the time that an object has been moving for is equal to its final velocity minus its initial all over acceleration. What I'm going to do now is I'm going to replace all the t's in this bottom equation with that identity, because t is equal to that, so I can replace t with that identity. Now I'm just going to carry out the algebra, and when I do that, this is what it looks like. I'm going to run through this kind of fast. If you want to pause and take notes, you are welcome to, because it gets a little ugly for a little while. So I'm just running through this algebra to try to simplify it into one big equation, and when I end up simplifying this, I get this shape, which I can rearrange by multiplying both sides by 2a, cancel that out. And when I add u squared to both sides, that is my fourth kinematics equation. So that proof is based on our knowledge of the other two equations, which itself is based on geometry. So that's basically a mathematical explanation of why all four kinematics equations work in the way that they do. It's all just based on the geometry of a graph. For those of you who know calculus, I can make a separate video explaining why these work in terms of calculus, but it's not really necessary that you know that for the class. This class does not require calculus. Just as a hint, though, those first two equations may ring a bell. They look very similar to integral functions, which you might have taken in calculus. So that's a hint if you want to start working on that on your own. But that's what you need to know for this video, just the basic proof using geometry. Thank you for watching. Now that you've learned how to apply the kinematic equations in a bunch of big general situations, I need to show you how to apply them in one very specific situation, which we call free fall. So the definition of when an object is in free fall is pretty simple. The definition is if the only force acting on an object is the force of gravity, we say that the object is in free fall. And all objects in free fall accelerate at the acceleration of gravity. This is symbolized as lowercase g, and on Earth, g is always 9.81 meters per second squared for any object that we're dealing with. The mass of the object does not matter. All that matters is that the object is on or near planet Earth, so it will always accelerate downwards at 9.81 meters per second squared. And again, we symbolize that with lowercase g. That's the symbol for the acceleration on Earth specifically. And the acceleration always points straight down toward the center of the planet. So in most of our situations, it's just going to be straight down. That's all we have to think about. So right now, this apple in the picture is not in free fall because there's the force of gravity trying to pull it down to Earth, but there's also a force from the hand pushing it up in the other direction, keeping it up. But when I take the hand away, the only force on the apple is gravity, so now it is in free fall. And it will continue to be in free fall until it hits the ground, when the force from the ground pushes up on it and it stops it from falling. So as long as that apple is moving through the air with nothing supporting it, it is in free fall. An important thing to remember about the acceleration of gravity is that it is always accelerating everything straight down at 9.81 meters per second squared, even when the object itself is moving upward. So even if it's moving up, the gravity is pulling it to a stop and then pulling it back down in the other direction. So that acceleration is always going to be pointing straight down. So if I were to draw a kind of map of what the acceleration of an object looks like at different points along its path, it's always going to be exactly the same. It's always going to be that 9.81 downward. It's the velocity that's changing. The velocity starts very big, but because the acceleration is pointing in the opposite direction, the velocity becomes smaller, and then at the very top of the object's motion, it's 0, and then it begins to point in the negative direction and then more in the negative. So this is something that confuses students a lot. They think that the acceleration itself changes when an object is moving up and then moves down, but that's not true. The acceleration is always 9.81 meters per second downward. It's the velocity of the object that's changing. The velocity can start very positive, go to 0, and then become very negative as the acceleration continues to change it and pull it more in the downward direction. So knowing that an object is in free fall gives you specific information you can use in kinematics equations. So these are three things you know when an object is in free fall. The acceleration is always going to be g, which is 9.81 meters per second, and always pointed downward. So if your downward direction is positive, your acceleration is going to be positive 9.81. And if your downward direction is negative, the acceleration is going to be negative 9.81. And you also know in some free fall problems, it might say that the object is dropped. That's kind of physics code, which means that its initial velocity is 0 meters per second. Because if you drop an object, you're not giving it any velocity to start off. You're just letting it go, and the acceleration of gravity is speeding it up, but it's going to start with that initial velocity of 0. The third rule is that if the object is thrown upwards, its velocity at the very highest point of its motion is going to be 0, because before that, it had a velocity going up, and after it has a velocity going down, so it's crossing from a positive to a negative, or a negative to a positive velocity. And when you cross from a positive to a negative, you hit 0. So the object stops moving for an instantaneously small second at the very top of its motion before beginning to fall again. I'm going to show you a few examples of how these rules work, and then you're going to have some chances to try this on your own. So let's say you have a problem that says a ball is dropped from a height of 10 meters. What will its velocity be right before it hits the ground? So before I fill in any values, I have to decide which direction is positive and which direction is negative. For now, because the object is only going to be moving down, I think it would be easy to consider down to be positive. So, that way I'll only be dealing with positive numbers. So if down is positive, I know that acceleration is 9.81 meters per second down, so that's going to be positive as well. The displacement of the object is going to be positive 10 meters because it's moving 10 meters down during its fall, because that's its height that it starts from. And its starting velocity is 0 meters per second because it's dropped. Again, that's physics code. That just means that it starts with no velocity. And we're trying to figure out its final velocity. So looking at our table of kinematics equations, you'll remember that all I need to do is find the equation that has all the things I have, the things I need, and nothing else. And in this case, that's going to be this fourth equation right here. So I just take this, plug in the numbers, and I find that the final velocity of this object is going to be 14 meters per second. And because that velocity is positive, that tells me that because I set down to equal positive, that velocity is 14 meters per second downward. Here's another example. A ball is thrown up at 10 meters per second. What is the maximum height it will reach? So here I'm going to consider up to be positive, just because this is the only direction that the object will actually be moving in this problem. Because if we're talking about its maximum height, we only care about the maximum height that it will rise to. We don't care about what it does after. So if up is positive, and I know that it's thrown up at 10 meters per second, that means that its starting velocity is positive 10 meters per second. And because acceleration here always points down at 9.81 meters per second squared, that acceleration is going to be negative because it's pointing in the opposite direction of the positive direction. We're trying to find the displacement here. We're trying to find the maximum height that the ball reaches, which when you think about it is the displacement from when the ball leaves the hand to that final point. And this is really important. We know that the final velocity of the ball in this problem is going to be 0 because at its maximum height, it will have a velocity of 0. And we want to end this problem when the ball is at its maximum height so that we can find that maximum height. So looking at the kinematics equations, this last one works a second time. So I'm going to bring this up, plug in numbers. The positives and negatives matter a lot here. Need to respect those. So I find that the displacement of the ball is 5.1 meters in the upward direction. So if you throw a ball upward at 10 meters per second, it's guaranteed by physics that it will go exactly 5.1 meters up into the air. So asking another question about the same situation, we can now ask how much time will it take for the ball to reach its maximum height. So using up as positive again, you'll remember that the initial velocity is 10 meters per second up, the acceleration is negative 9.81 meters per second, the velocity is 0 meters per second, and this time we're trying to find t. And if we're trying to find t, we can use this first equation here that has everything we have and what we need. So when I plug this in, I find that t by itself is equal to 1.02 seconds. That's how long it takes to get up to that maximum height. We can also split free fall problems into multi-step problems. That's pretty easy as long as we consider each step and how they're connected. So as an example, we can ask a ball is thrown off a cliff at 20 meters per second up. The cliff is 50 meters high. If the ball falls all the way to the ground at the bottom of the cliff, how much time will it take to reach the ground? So the first part, we need to answer how much time passes as the ball is moving up. And the second part, we're going to need to answer how much time passes as the ball is moving down. And then after we figure out how much time it takes to go up and how much time it takes to go down, we can just add these two times, and that will be the total time. So solving for part 1 first, how much time does it take the ball to reach its maximum height? I know that it starts with a positive velocity of 20 meters per second. If I'm considering up to be positive, its acceleration is negative 9.81 and its velocity is 0. And if I plug these into my kinematics equations, I find that the time there is 2.04 seconds. I'm also going to need the displacement of the ball just to figure out how far it falls in the second half of the problem. So I'm going to figure that out with another kinematics equation. When I plug this in, I get that the displacement is 20.4 meters. So I'm just going to write that in here. So my time for part 1 is 2.04 seconds. That's how long it takes to reach its maximum height. For the second part, I'm just asking how much time it takes the ball to fall from its highest position to the ground, and so I can see that it has to fall a total of 70.4 meters, because it's the full 50 that it started with, plus the additional 20.4 meters that it gained. And that displacement is going to be negative because it's falling in the downward direction, and I've defined up to be positive. So my starting velocity for the second part of the problem is 0, because that's how much it ended with in the first part. It was at the very top of its motion, and again, its acceleration is negative 9.81, its displacement is negative 70.4, and we're trying to find the time. So we plug this into a kinematics equation, and I find that the time here is equal to 3.78 seconds. And so I just add that with the first part to get a final total time that the ball is in the air of 5.82 seconds. So that probably seemed pretty complex. If you lost me there, it's totally okay. I just need you to get the notes down as an example. Once you do a few problems with this, it will become much clearer. Just remember those 3 rules. The acceleration is always 9.81 meters per second squared down. If the object is dropped, its initial velocity is 0 meters per second. And if the object is thrown upwards, its velocity at the highest point of its motion is 0. This lecture is going to be about two-dimensional projectile motion, and the first thing we're going to do is define those 2 words. So for something to be two-dimensional, it means that it's happening on 2 perpendicular axes at the same time. A dimension is an axis of motion that you can move on, and that is at a 90-degree angle to other axes. So far we've been talking about motion that happens in just one dimension. That means back and forth along a straight line. But it's possible for motion to happen in 2 dimensions at the same time, where it's moving up and down and left and right. And it's also obviously possible for motion to happen in 3 dimensions, which is something that we'll talk about in future units. But for now, we want to focus on 2-dimensional motion specifically. And a projectile is any object with only the force of gravity acting on it in free fall. We talked about this a little bit in the acceleration unit when we talked about falling objects. So as long as this object is in the air, it's a projectile, and as long as the only force acting on it is gravity, it's a projectile. So 2-dimensional projectile motion means movement of an object in both a horizontal and vertical direction where gravity is the only force present. As it turns out, this is a really important topic to understand in physics because a lot of objects in the world fit this description. So if we watch this ball being launched, you can see on my y-axis that it's moving up and down in the y-axis, and it's moving from left to right on the x-axis as well. So it's 2-dimensional motion because it's moving along both axes. So the forces on a projectile are a little counterintuitive. If we draw the chart of the forces at different points, it's always only going to be the force of gravity. There's no other force acting on a projectile. Later on in this unit, we'll talk about forces of air resistance that can act on projectiles, but for most physics problems, we assume that air resistance is not there. So the only other force that can be acting on this projectile is the force of gravity. The reason why it's still able to move from left to right is because of Newton's first law. Newton's first law says that if there's no force on an axis, that means there's no change in velocity along that axis. So if this projectile starts with some x velocity, it's going to continue having that x velocity through the entire trip. So if it's moving to the right at 5 meters per second, it's going to continue to do that because there's no force in either direction to stop it. The acceleration of a projectile is always 9.81 straight down because, again, the only force acting on it is gravity, and gravity on Earth accelerates everything at 9.81 meters per second down. And the velocity of a projectile is the way that it's actually moving the direction of its motion. We can break this into its x velocity and y velocity, how fast it's going in the x direction and how fast it's going in the y direction. And the x velocity is going to stay the same the whole time. If you're able to find a projectile's x velocity at any one point along its motion, you'll know that that's the same velocity for all other points along the projectile's motion because there's no force to speed it up or slow it down in that direction. So that means that the x velocity for a projectile is going to stay the same through the whole motion. The y velocity, however, is being changed because there's a downward acceleration of gravity. So for my example here, this particular projectile starts with a very positive upward velocity, but as it rises, it slows down in the upward direction because acceleration is taking away from it. It's being added to in the negative direction. At the very top of its motion, you may remember from the unit on acceleration that there's no y velocity at the very top, because what's happening at the very top of its motion is that it's slowing to a stop and then beginning to fall again in the other direction. And then as it falls, it starts to get faster and faster in the negative direction because gravity is still accelerating it down. So these are the x and y velocities, and to understand what the overall velocity looks like, I just need to do vector addition by combining the tip of one vector to the tail of the other and then drawing that new connecting vector. And these are the resulting velocities at each point, which kind of fits our experience of a projectile. It starts going up at a large angle, but then slows until it's only moving perfectly horizontally and then begins to fall again. So this is what the velocity of a projectile tends to look like. Okay, this sentence is the fundamental idea of 2D projectile motion. This is kind of the guiding idea that we use to solve most of the problems in this unit. Kinematic variables on one axis are independent of kinematic variables on the other axis except for time. We can use a separate set of kinematic variables for each axis to predict the object's motion along that axis. So if I look at what the object is doing along the y-axis versus what it's doing along the x-axis, there's no clear relationship there. Like it's moving up and then down along the y-axis, but it's only moving rightward along the x-axis. So these two things are independent of each other. So we can come up with two separate kinematic tables, one for the x-axis and one for the y-axis, where we find missing information about the object. So we're going to begin every single 2D projectile motion problem by making these tables for the x and y kinematic variables. And again, notice that time doesn't have a direction. It will be the only variable that is the same in both. These are some general rules for how to solve a 2D projectile motion problem. Because gravity is the only force on the object, the x direction acceleration will always be 0, and the y direction acceleration will always be 9.8 meters per second down. Whether you consider down to be positive or negative is going to depend on what you want to do in that particular problem. You just need to make sure that it is consistent with your other variables. The second thing to know is that you can only use kinematic equations on one table at a time. At no point can you put x-axis variables and y-axis variables together into a single kinematics equation. So you can only work with one table at a time in these problems. And time is the only variable that is the same in both, and if you don't have enough variables on one table, you should solve for time on the other table and bring it over to the table that's missing variables. You'll remember that you need at least 3 kinematics variables to use the kinematics equations, so if you only have 2 on one table and you don't have time, you can solve for time on the other table, bring it over, and solve some problems with it. I'll give you a few examples of that in just a moment. These are some code words for projectile motion. Launched horizontally or falls off a flat surface means that the object has no initial y velocity, or the y velocity is 0. The highest point in its motion, or the maximum height it reaches, is where the y velocity is equal to 0. So that means that if you're dealing with the highest point that an object reaches, that is the point where the final velocity of the object is 0 meters per second in the y direction, not in the x direction. The x direction stays the same, but in the y direction, it's 0. The range is the total x displacement of a projectile, and if the object lands at the same height it started with, its y displacement is going to be 0, because if it goes up and then down, it's at the same place where it started, so its total displacement is 0. Let's use these concepts to solve a few problems. A ball rolls off a 1.5 meter high table at 2 meters per second. How far away from the table will it land? So that's the ball's motion, and we're trying to figure out how far away from the table will it land. I'm going to call rightward my positive direction on my x-axis, and I'm going to call downward my positive direction in the y-axis. Just because this object isn't moving up at all, it's only falling down, so it'll be easier to call down positive. And I know that because there's no force in the x direction, the acceleration in the x direction is 0, and in the y direction it's 9.8. This is true for all 2D kinematics problems. And here I'm calling down positive, so that 9.8 in my y direction is positive. And the goal of the problem is to find how far away it is from the table, which is its x displacement. It's how far it's moved horizontally. Vertically, I can see that it's moving 1.5 meters, but horizontally, I don't know how far it moves. So that's the thing I'm trying to solve for. I can also see that in the x direction, it's moving at 2 meters per second perfectly horizontally, so that means that it has a horizontal x-axis velocity of 2 meters per second. And because that's pointing to the right, I'll call that positive and put that in the initial velocity. And in the y part, it's moving down at 1.5 meters of displacement. So because I'm calling down positive, I'm calling that 1.5 meters positive as well. And because it's moving in the perfectly horizontal direction to start off, that means that it's not moving up or down at all in the moment when it starts its projectile motion. So if it's not moving up or down at all to start off, that means that its initial y velocity is going to be 0. That's all the information that we can get from the beginning of this projectile problem. Most of the challenge of solving projectile motion problems really comes from having to read out that information and understand what it's telling you. After you do that, the rest is pretty straightforward. You just look for what you're trying to look for, and I can see that I'm trying to find the displacement in the x direction, and I can see that I only have 2 other variables in the x direction, so I don't have enough in that table to solve for the displacement. So what I can do is try to solve for time on the y-axis table, and then bring time over, because the time that it falls is going to be equal to the time that it's in the air in the x direction as well. So looking at my y table, I see I have s, u, a, and I need t, and the only thing that connects those is this second kinematics equation. So when I plug in my numbers, I get t by itself is equal to 0.56 seconds. So that's the total time that it's in the air before it falls the full 1.5 meters. So that means that it's also the time that it's in the air in the x direction. So I can take that over into the x table, and now I can solve for the displacement. And I can see I have s, u, a, and t, so I'm actually going to use that same equation, but this time I'm solving for s. And when I do that, I get 1.12 meters. So that means that if you launch a ball off a 1.5 meter table at 2 meters per second and there's no air resistance, it will go exactly 1.12 meters away from the table. This is example number 2. A ball is launched at 10 meters per second at a 30-degree angle above the horizontal. How far away will it land? So this is the motion of the ball, and we're trying to figure out how far away it lands. I'm going to call the rightward direction in the x-axis positive and the upward direction in the y-axis positive. You can choose which directions are positive and negative on your own. That's okay, as long as they're consistent. Just like with all 2D projectile problems, I know that the acceleration in the x direction is 0, and the acceleration in the y direction is 9.8 down, which because up is positive here, I'm going to have to call down negative, so that acceleration is negative. That's going to be really important for solving these problems. And I can see that I have a problem where the initial velocity isn't in the x direction or the y direction. It's in both. It's moving both horizontally and vertically at the same time. So to figure out how fast it's going in the x direction and y direction, I can find the x component and y component of that velocity using trig. One more thing I can see is that the total displacement in the y direction is 0 meters because it's going up but then falling back down to its original position. So it didn't actually move in total in the up-down direction from the place where it started. So its total displacement in the y direction is 0. Solving for those initial velocities in the x and y direction using trig gets me these answers. In the x direction, it's 8.7 meters per second, and in the y direction, it's 5 meters per second up, which is positive. And if I'm trying to figure out how far away it will land, I need to find the displacement in the x direction. Just like last time, we don't have enough variables in the x direction to solve for the displacement, but we can solve for time in the y-axis and then take it over to the x-axis and use that to solve the problem. So I'm going to start by solving for time, and I have s, u, a, and t. So just like the previous problem, we're going to use the same equation, and when we do that, we get time is equal to 1.02 seconds. And because time is always the same in both axes, the time in the y direction is equal to the time in the x direction, so I can use that and the same equation to solve for the displacement. And when I do that, I get that the total displacement of the ball is 8.9 meters. Here's one more example. A ball is launched at 10 meters per second at a 30-degree angle, same as before, above the horizontal. What will be its velocity after 0.3 seconds? So I'm keeping the same variables that I knew before, only this time it's not coming to land. We're not analyzing the spot where it lands yet. We're analyzing a previous spot. So if I'm trying to find its velocity, that means its total velocity, not just its velocity in the x direction or the y direction. So to solve for that, I'm going to have to find each individual x and y velocity and then put them together to find the total. So I'll start in the x direction. Looking in the x direction, I have u, a, t, and I need v, so that's going to be the first equation. And when I solve for that, I get v final is equal to 8.7 meters per second, which makes sense because if the acceleration is 0, the velocity isn't changing in the x direction. And in the y direction, if I plug in my values for u, a, and t into that same equation, I get final v is equal to 2.1 meters per second. So if it moves and is in the air for 0.3 seconds, this is how fast it's going in the x direction and the y direction. So now that I have the x direction velocity and the y direction velocity of the projectile when it's been moving in the air for 0.3 seconds at that point right there, I can figure out the total velocity in this way. I know that the x velocity is this much and the y velocity is this much, and these are two individual velocity vectors. The total velocity is going to be the vector sum of the two, which means a single new vector drawn from the tail of the first to the tip of the last, which looks like this. And when I plug those into the Pythagorean theorem, because this is forming a right triangle, I find that the hypotenuse of that triangle is 8.9 meters per second. So that would be the ball's total velocity after that amount of time. So those are a few examples of solving projectile motion problems. You're going to get a lot more as the unit goes on. This lecture is going to be about the effect of air resistance on projectiles. Air resistance is the force of air on objects moving through it. The more velocity an object has, the more air pushes back against the object's velocity. So in this case, we can imagine the space ball getting faster and faster through the air in this direction, and as a result, the force of air resistance gets bigger and bigger on the ball. So air resistance is always working perfectly against the direction of the velocity. So if the velocity is pointing in this direction, the air resistance will push back up in this direction. This creates a pattern where the faster an object is moving through the air, the more it is accelerated in the opposite direction, because air resistance is pushing it back, and there's usually nothing pushing it forwards. So if it starts off moving fast, it's rapidly slowed down because there's a lot of force of air resistance on it. But as it loses velocity, the air resistance also goes down, which means that the force slowing the object down is itself getting smaller, so it actually slows down at a lower and lower rate. So it takes longer to slow down if you're moving at a slower velocity through the air. So the rate of slowing itself slows down as you slow. A lot to take in there. Hopefully this visual helps a little bit. We can see the effect of air resistance on the shape of the path of projectiles. This is an example of an object moving without air resistance. And the noticeable thing about an object moving without air resistance is that it forms the shape of a perfect parabola. This is because its motion in the x direction is constant and its motion in the y direction is symmetrical. Whatever it's doing on one side, it's doing the opposite on the other side. And so another thing that's noticeable here is that the displacement for the first half of the object's motion in the x direction is perfectly equal to the x direction displacement in the second half of its motion. It's symmetrical in that way. So if you see an object that's moving parabolically that's perfectly symmetrical, you know that there's no air resistance applying on the object. Now let's apply air resistance to this ball and see how its motion changes. So you'll notice that the path is different. It doesn't go up as high and it doesn't travel as far. And you'll also notice that it travels farther in the first half of its motion than it does in the second half of its motion. This is because as it moves forward, the velocity vector is being slowed down by the force of air resistance. So that means that it's moving slower in its second half of motion compared to the first. So in the second half of its motion, it moves less far in the x direction than the first. And the force of air resistance is also stopping it from going up as high. So you can see that the displacement in the x direction in the first half of its motion is much larger than the displacement in the second half of its motion, and it doesn't achieve the same height. So that will be the shape of projectiles with air resistance. We can also graph the motion of objects that are experiencing air resistance with position, velocity, and acceleration graphs. We normally only pay attention to the y direction of an object that's experiencing air resistance when we're graphing it. The x direction graphs don't really come up as much, so I'm only going to focus on those for this lecture. Let's start with an object that's free falling through the air, or it starts in free fall, but as it moves through the air, air resistance begins to pick up. So in the second that it's dropped, it's accelerating down at 9.81 meters per second, because in the second it's dropped, it doesn't have any velocity yet. So the only force acting on it is gravity, because no velocity means no air resistance up. And if the only force acting on it is gravity, that means that it starts with 9.81 meters per second squared of acceleration. And I'm considering the downward motion to be positive here, which is why that's on the positive part of my graph. But as it falls, it starts to pick up velocity very quickly because it has a large downward acceleration. So as it picks up velocity quickly, it also picks up air resistance very quickly. But as it gets more and more air resistance, it's also getting less and less total net force because the air resistance is working against the force of gravity. So the less net force it has, the less acceleration it has in the downward direction, which means that it takes longer to get more velocity, which means it takes longer to get more air resistance. So the more air resistance you have, the harder it is to get even more. So that's why the acceleration graph here is curving down. It starts off very easy to get more air resistance, so the acceleration rapidly drops off. But as you keep going, it becomes harder and harder to get more air resistance and add to that. This continues in this pattern until you hit a point where the acceleration finally becomes zero, where the air resistance balances out the force of gravity. And when this happens, this is terminal velocity. This is where the ball is moving at its fastest possible velocity and can't get any faster because the acceleration is zero because the forces are balanced out. So that point at the end of the graph is where terminal velocity occurs for the acceleration graph. We can also look at the velocity in the y direction for this object. We can imagine again that it's dropped, so that means that it starts at zero, and as it accelerates, it starts off gaining a lot of velocity in a little time, but as air resistance begins to apply to it, it becomes harder and harder to get additional velocity until the air resistance perfectly balances out the force of gravity. One way that we can understand this is to refer back to our acceleration graph. So I put the acceleration graph below the velocity graph to the left of my head, so you can look at what the graph's doing as you look at what the velocity graph is doing. Remember that the slopes of the tangent lines on a velocity graph represent the acceleration. So if the acceleration starts very positive but rapidly decreases, that means that the slopes of the tangent lines are also going to start very positive but rapidly decrease. But as they keep going, they're decreasing at a slower slower and slower rate. So they're getting to zero at a slower and slower rate as the graph goes on, until at the very end it finally hits zero. So the point where the acceleration is zero, that's where the velocity graph will have a flat slope. So it's just staying at that constant velocity. So that point there, that constant velocity, is the terminal velocity of the object. That y-axis value is the terminal velocity of the object. We can also look at the acceleration and velocity graphs of objects that are moving from one medium to another medium. Let's say, for example, that we drop this ball above the ocean and see what happens as it falls, and then when it hits the water and moves into the water. So the second that we drop it, it starts off with an acceleration of 9.81 because the only force on it is gravity, and it starts with a velocity of 0. But just like in our previous graphs, these two graphs curve in this way until it hits its terminal velocity. So at the line that I drew, that's where terminal velocity happens on the graph, and that y value on the velocity graph is the exact terminal velocity of the ball in the air. So it hasn't hit the water yet, so it's going to continue to fall at that same terminal velocity, so the velocity is staying constant, which means that the acceleration is staying at 0. And then at this moment is where the ball hits the water. And when the ball hits the water, it's no longer feeling the force of air resistance pushing it up. It's now experiencing a buoyant force, which is the name for the force from water. And water pushes back on things much more strongly than air does. You know, it's much easier to move your hand through air than it is through water. So that means that suddenly there's a much larger force pushing up on the ball than there is pushing down. So that means that the net force is pointing up. So that means that the acceleration is also pointing up on this ball, which means that on my graph, the acceleration is suddenly going to jump into the negative value because we're considering down to be positive, so up is negative. For the rest of the ball's trip, it's going to slow down because the acceleration is pointing up while the ball moves down through the water. So that means that the acceleration is taking away from the velocity. So the buoyant force is going to shrink because as you slow down, as the acceleration takes away from you, you're moving through the water less quickly. So the water is putting a smaller and smaller force back on you. So this is what the next part of the graph would look like. So it continues to slow until the buoyant force balances out the force of gravity. And when it does that, the ball is now at a new, smaller terminal velocity because it was slowing that entire time. And the forces are balanced, so the acceleration is now 0. So this is the new terminal velocity of the ball in the water. And if nothing interrupts that, it will just continue to fall at that rate until it hits the bottom. So obviously that graph is very complicated. If you watch this a few more times and try to take in every little bit of information, there's no one part of it that's especially challenging. It's just understanding everything that's happening. That's a lot to take in at once. This exact same graph can also apply to other physical situations. Skydivers are really popular in physics when talking about air resistance. So when the skydiver dives out of the plane, the only force on them in the moment they dive out is the force of gravity because they're not moving yet, so there's no air resistance. So that means that their acceleration starts at 9.81. And as they begin to fall, the force of air resistance gets bigger and bigger and bigger. So those first parts of the graph are the same as before until the skydiver hits a terminal velocity without their parachute. And then they can fall at that terminal velocity for a certain amount of time. And let's say this is the point where their parachute opens. And the parachute makes their force of air resistance much larger because it has such a large surface area. So suddenly the net force is pointing up, which means that the acceleration is also pointing up, which means that because on my graph up is negative, the acceleration is suddenly going to jump to being very negative. So now that the velocity is still positive, but the acceleration is negative, the acceleration is going to rapidly take away from the velocity. And as the velocity gets smaller, the force of air resistance gets smaller until it balances out with the force of gravity again. And by that time, the velocity has gotten significantly smaller, so now the person is at a new terminal velocity with their parachute that they will maintain until they hit the ground. This is the reason why people use parachutes when they skydive. It's because when you open the parachute, you achieve a much smaller terminal velocity so you can land safely. You're not going to have to do specific math with these types of graphs. The important thing is to understand why the patterns in them are the way that they are, why they're curving in certain spots, why they're staying flat in certain parts, and what those curves and flat parts mean in relation to the forces and the velocities.
This is a quick video on how to draw a motion map, which, like the title implies, is a way of representing motion. There are very specific rules to drawing one that we're going to go over. The first step in drawing a motion map is to decide on a 0 point and then draw an arrow to represent the positive direction. Both of these are entirely arbitrary. You can choose any point you want to be the 0 point. In general, that's just a common point where we measure other positions from. So if you're 2 meters in the positive direction away from the 0 point, we would say you're at a position of positive 2 meters. Totally arbitrary, so you get to decide where that is. On the motion map, it's going to look something like this. We're going to draw a point and say that this is the 0 point, and then draw an arrow coming out of it and indicate that that is the positive direction. So if an object is moving in the opposite direction of the arrow, it's moving in the negative direction. So I can now give you an example of drawing a motion map itself. What a motion map does is it puts dots at the position that an object is at after different amounts of time has passed. Usually there's 1 dot for every second of time. So for example, if we had a car starting at the 0 point here, and the car started to move, I would put a point where the car is for every second that the car had traveled, like this. So I'm going to put a point where it starts, and then as it moves forward, I'm going to add a point for every second that it's traveled. So we don't actually represent the physical car on the motion map. This is what your motion map is going to look like when you actually draw it. No matter what object you're drawing, you're just going to draw points representing its position at different amounts of time. And you can see that the exact position is kind of arbitrary. Motion maps aren't always used very specifically. Sometimes it's just a general picture of what an object is doing. The next thing to do is to label these points with the time that it was when we drew them. So this is what that would look like. Before time had started, that was the first point, and then time is equal to 1 second, 2 seconds, 3 seconds, and 4 seconds. So the dots show where the object was after each second passed. The next thing to do is draw arrows connecting each dot from where the object started to where it stopped. The reason why we draw these arrows is because the arrows show the size of the velocity. Because velocity is displacement divided by time, and time is just 1 second for each dot, an arrow that shows the length of each interval also shows the size of the velocity. So if there's a larger distance between 2 dots, that means that in that 1 second you were going faster, because the same amount of time passed, but you crossed a larger distance. So the arrows are a useful way of representing how fast you are going on the motion map. So fast objects cover more distance in the same amount of time, and their velocity vectors are larger. So we can compare a faster car and a slower car like this. And you can see that if I draw a dot for every 1 second that passes, the faster car has larger arrows than the slower car, because the slower car was covering less distance, so the dots are going to be closer together. If an object is standing still, like if we have a cow sitting here and it's just standing still, we just draw the same dot every second, and we're just going to put that dot above the previous dot like this, just so we don't keep drawing in the same place over and over again. So if you have dots that are kind of piling on each other like this, what this means is that the object is standing still in one specific spot. To show an object moving in the negative direction, we just have it move in the opposite direction of your positive direction. So this is an example of the car moving in the negative direction. And you could also draw arrows pointing to the left to connect those dots. We draw a double arrow above the first arrow to show the acceleration of the object. These arrows show how much the velocity increases or decreases in 1 second, the definition of acceleration. With every second, the velocity arrow will get 1 acceleration arrow length larger or smaller. So I'll show you an example. Let's say that at time equals 0, there's no velocity, but there is an acceleration arrow. So this acceleration arrow is showing you how much faster you'll be going after 1 second. So it's going to show you the increase in the velocity arrow in 1 second. So after 1 second, the velocity is going to be the acceleration arrow plus 0, because there's no velocity to start off here. So it's just the acceleration arrow's length. And then after 2 seconds, the velocity arrow is going to be the acceleration arrow bigger than it was before, like this. So the acceleration arrow is showing you how much the velocity arrow is growing over time. So we can do that again. We're assuming that the acceleration is just staying constant here, which it always does. It's very rare to get a changing acceleration. So we connect that arrow and see that it's getting bigger and bigger and bigger. So you can see that we can use these acceleration arrows to show you how much faster the object is getting per second. If the acceleration arrow is pointing in the opposite direction of the velocity, like I'm imagining that this is starting with a very large positive velocity, if it's pointing in the opposite direction, that means that the acceleration is actually slowing the object down. It's getting slower over time. So if I combine the acceleration arrow with the velocity arrow like this, you can see that it's pushing back against it, and so the new velocity will be smaller than before, and it keeps pushing back against it, so it becomes smaller and smaller and smaller. So acceleration arrows pointing in the opposite direction show you how the velocity is getting smaller over time by that exact amount. And that's everything that you have to know about drawing a motion map.
This video is going to be about forces and free body diagrams. I'm going to start by defining what a force is. A force is a push or pull on an object, and because every push and pull has a magnitude and a direction, forces are vectors and can be represented using vector notation. Forces are measured using the unit newtons, or capital N for short. So if you push on this box, that has a magnitude and a direction. There's no way that your push cannot have a certain size and a certain direction. And we could measure the push with a number followed by a capital N. So I could say you push the box with 100 newtons of force, and that makes sense. That's how we communicate the size of a push in physics. I can represent a smaller push with a smaller vector and say that this is 50 newtons. Because a force is a vector, we can add multiple vectors together in the same way we add regular vectors. So if you're pushing on this box with 100 newtons and I'm pushing back with 80 newtons, altogether, the sum of all forces acting on an object is called the net force on the object. This is maybe one of the most important ideas in all of physics, the idea of a net overall force that is applying on the object, so you're going to have to pay close attention. A net force is just the sum of all the vectors of forces acting on the object. So here, the net force would be 100 minus 80, because 80 is working against that 100, which you can see would be 20 newtons to the right. So if you're pushing with 100 newtons to the right, I'm pushing with 80 back to the left, the total overall force on this box is just 20 newtons to the right, which kind of makes sense given our experience. So the net force here would be 20 newtons to the right. To show all the forces acting on an object, physicists create a free body diagram, which is a box or dot with vectors coming out of it showing the magnitude and direction of all the forces acting on an object. So we don't really want to have to make drawings of all the objects that we have forces on. So instead we represent those complex objects as just simple squares or dots. So this is an example of a free body diagram, just a simple square with forces coming out showing the size and direction and names of all the forces on an object. And as you can see, we can also represent it using a dot. Another advantage of free body diagrams is that they allow us to see the vectors very clearly, and so allow us to add all the forces together to find the net force. So as an example, these added together would result in this net force. And so the way that you find that net force is going to be by taking all the x components and all the y components of all the forces on your free body diagram and adding them together like we did in that previous example. So you just keep combining them until you have a single x, a single y, and then use the Pythagorean theorem to figure out the overall net force on the object. So this is all that you have to know for this video. Because force is a vector, we can add multiple forces together in the same way we have vectors. The sum of all forces acting on an object is called the net force on the object. And to show all the forces acting on an object, physicists create a free body diagram, a box or dot with vectors coming out of it showing the magnitude and direction of all the forces acting on an object. So those are some definitions that you need to know for now. We're going to start practicing with those in this class. This lecture is going to be about properties of common forces that are going to reappear again and again and again, and that you're going to use for problem solving in this unit and in future units. I'm just going to start and go through the definition and properties of each force. The first force we're going to talk about is the force of gravity. This is created between any two objects with mass, and the more mass, the more gravitational force is present. The largest mass near us is the Earth, so we feel its gravity most strongly. And the force of gravity on Earth always points straight down toward the center of the Earth. And the force of gravity on an object is also called its weight. Weight is equal to mass multiplied by the acceleration of gravity. So let's say that we have this apple with a mass of 0.4 kilograms. The equation for weight is equal to mass times lowercase g, which if you remember from previous problem solving is equal to 9.8. So I would find that the weight is equal to 3.92 newtons of force. And the weight always points down. The force is a vector. So I draw it as a vector on this object, 3.92 newtons pointing straight down. So gravity is going to be present in basically all of the problems that we do in this class, almost all of them anyway, because almost all of them take place on Earth or on another planet. And gravity is always present there, pulling straight down.
So if this is 5 kilograms, we know for a fact that one of the forces on it is the weight, which is just equal to 5 times 9.8, which is equal to 49 newtons. This is a common misconception. If an object is on a ramp, a lot of students will mistakenly draw the gravity like this, pointing straight into the ramp, but that is not correct. The force of gravity always points straight down like that. That is going to become extremely relevant in a few days. For now, you just have to remember, even on a ramp like this, the force of gravity points straight down. Next up, we have the normal force. This is the force created by a surface to oppose a force pushing on it. The word normal in math means at a 90-degree angle to, and the normal force has its name because it always acts at a 90-degree angle to the surface that is creating it. The normal force always perfectly matches whatever net force is pushing the object into the surface. So basically, when you hear the word normal force, I want you to think the force created by a surface to stop the object from falling through the surface. So if this box is resting on the ground, we know that it has a force of gravity pulling it down of 98 newtons based on the previous definition, but it doesn't fall through the ground. That means that there must be some other force pushing it up, and this we call the normal force, the force that the ground is putting up on the box to support it. And the normal force always perfectly matches whatever net force is pushing the object into the surface. And you'll notice that it's at a 90-degree angle to the ground, so that's why we call it the normal force, and it's also 98 newtons to match the force of gravity. If I were to push down on this box and give it an additional force into the ground would actually push back up with exactly as much force to balance out the total force going down. So if I add in an additional 102 newtons with my hand, plus the 98 newtons of the box's weight, the ground automatically knows to push back up with 200 newtons of normal force to perfectly balance out the forces and make the total equal to 0. And if I were to pull up on the box to kind of assist the ground would kind of know that it didn't have to apply that extra 40 newtons to keep the box in one place, and so it's actually going to decrease by 40 newtons, and the normal force would now be 58. So it's really just whatever force it takes to stop the object from falling through the surface once all the other forces on the object are accounted for. The normal force doesn't just point up and down. If you're pushing on a surface sideways, the surface is going to give you the exact same amount of force back in the other direction that you're putting on it, and that is also an example of the normal force, because again, it's at a 90-degree angle to the surface, and it's created by the surface. The next type of force we're going to talk about is the force of friction, that's symbolized as F lowercase f. That's the force created by a surface on an object that opposes the object's motion. Friction always acts parallel to the surface and in the opposite direction of the object's motion. Its strength depends on the material of the surface and the object itself. There are two types of friction that we're going to go much more deep into in a future video. Static friction, which prevents an object from moving and balances out forces acting parallel to the surface, and kinetic friction, which acts against a moving object's velocity and always points opposite to the velocity. So as an example, if you give this box a push and the box does not move, that's an example of static friction pushing you back, and even if you begin to move, that box will still have the force of kinetic friction on it, but we're going to talk about that more in future videos. If a box is standing still on a ramp, that's probably because the force of friction is preventing it from sliding down. Next, we have the applied force. This is the simplest type of force. It's just the force of a push or pull from a person or another object. So if you put a force on this box, we would consider that to be the applied force, or F lowercase a. And if this billiard ball hits another billiard ball, it applies a force on it, so we would call that the applied force as well. Next up is the force of tension. This is the force created by the pull of a rope or string. Tension always pulls in the exact direction of the rope or string itself. And this is super important. This is going to be really important for problem solving. Tension pulls with equal force and opposite direction on both ends of the rope. Here's an example of how we could solve problems with that. If we had this 10-kilogram box hanging down, we can see that it would have a 98 Newton force of gravity using our equation, and if it's not moving, that would mean that there has to be some other force supporting it of 98 newtons, which we can see is coming from the rope. And if the rope is pulling up with 98 newtons on that side, on the other side it must be pulling down with 98 newtons. So that top box must be supporting the bottom one with 98 newtons of force. So if you pull on the rope, then the rope pulls back on you with this much force, and the other end of the rope pulls on whatever object you're pulling on with that same amount of force. So that's how you communicate your force through the rope. You cause it to put a force on you on one side, and it puts that exact same force on another object on the other side of the rope. Next up is the spring force, which we'll talk about more later. This is just the force exerted on an object by a spring. The more the spring is stretched or compressed, the more force acts on the object. A spring does not apply any force if it is at its natural length, which means it is not stretched or compressed.
The force of air resistance happens when an object is moving through air. The air applies a force in the opposite direction. For example, when you stick your hand out the window of a moving car, you can feel the force of air pushing against it. An object experiences more air resistance if it is moving faster or if it has more surface area. A falling object reaches terminal velocity, or its maximum velocity, when the force of air resistance up equals the force of gravity down. So as you can see, as this object is falling through the air due to the force of gravity, it's getting faster and faster and faster. And as a result, its velocity is getting bigger and bigger and bigger. And while its velocity gets bigger, the force of air resistance in the other direction gets bigger, because the faster you move through the air, the more air pushes back on you. So here, air is pushing back up on the object until it perfectly balances out the force of gravity, and at that moment, the object stops accelerating and it hits terminal velocity. So we call terminal velocity the point where the air resistance balances out the force of gravity to stop the object from accelerating. It's still moving, but that's its maximum velocity it can reach. Parachutes employ air resistance to slow the object down and prevent them from having a very high terminal velocity. When you're driving in your car, a lot of times the only two forces to the left and right are a small applied force from the engine and air resistance pushing back against it. As long as you can push back against the air resistance of your car, that's basically all that you need to keep it going. So those are some common types of forces and their basic properties. We're going to be using these to solve a lot of problems, and you're going to get very familiar with them, much more through solving problems with them than this video, but this is a good intro just to give you the basic info that you can use to begin to learn and solve problems. This video is going to be about force webs. A force web is a diagram that shows an object, all the other objects that are directly putting a force on that object, and the type of forces being applied. To draw a force web, you're going to start by writing the name of the main object in your problem and drawing a circle around it, and then writing the names of every object that is directly putting a force on the object in step number 1, and drawing circles around them as well. Step number 3, you're going to draw a line between any two objects that are putting a force on each other, label the line with the name of the force, and this line represents the force. Sometimes objects put more than one force on each other, and for these, you'll just draw more than one line. So I'll give you an example. A force web draws all the objects in a problem in circles. Lines connect the circles to show forces on the object. So they're all going to look like this. So let's say that we have this person who's tripped and is falling through the air and is not being supported by anything. Here I can see that the force of gravity is acting on him, and that's it. That's the only force that's acting on him. And I know that the force of gravity comes from the Earth, like the entire Earth pulling down on you like this. And so these would be the two objects in my first problem, the person and the Earth. Those are the only two objects that are putting a force on each other. So between them is the force of gravity. The Earth is pulling the person down with gravity. And as we'll learn later in class, the person is actually also pulling the Earth up with gravity. They're putting a mutual force on each other. But we'll talk about that more later. So Earth is actually going to be an object in basically every one of your problems involving force webs, because gravity is basically always present anywhere near the Earth. Let's look at another problem. Here we have a book sitting on a table. So we know that the force of gravity is pulling the book down, and because the table is a surface, it's supporting the book by putting a normal force up on the book. So I can see here that because the Earth is still creating that force of gravity, that's going to be one of the objects in my problem, and the other object is going to be the table and obviously the book itself. So I can just connect these with the forces that they're putting on the book. So the book is putting gravity on the Earth, Earth's putting gravity on the book, and then I connect these, and the normal force is acting between these two objects. I could also talk about what's going on between the table and the Earth, but I don't care about that so much. I'm really just worried about the book. That's kind of like the main central object in my problem. Let's say that we have these two people trying to pull this cart in different directions. So on the cart, I have gravity, normal, the force of tension this way, and a smaller force of tension this way. So these are my objects involved in the problem: the cart, the Earth, the ground, and two ropes on either end of the cart. Some students get a little confused, and they're curious about why both the Earth and the ground are in the same force web. It seems like they're the same thing. And the ground is what I'm calling the immediate surface that the cart is on. That's putting a normal force on the cart. Whereas the Earth is putting the force of gravity on the cart. The Earth is the entire Earth. Literally everything that is on the Earth is putting the force of gravity on the cart. And then the two ropes attached to the cart are putting the force of tension on the cart. They're different sized forces, but we don't really represent the sizes of forces on force webs. Size really comes in with free body diagrams, but not with force webs. So that's how you would draw a force web for this situation. And that's all that you need to know about force webs. You can copy these 3 steps down if you would like, but the main goal is to have you do a ton of these problems so that you get good at them. This video is going to be about finding the net force on an object. And to find the net force, we always start by drawing what's called a force table. The table looks like this. I'm going to label what each part means. The top here means the sum of the forces in the x direction and the sum of the forces in the y direction. That symbol next to fx and fy is a sigma. It means the sum of, so that just means what's coming below is equal to all the forces added together. In the next part of the table, you're going to add together all the horizontal forces that appear in your problem and all the vertical forces that appear in your problem. And then on the very bottom, you're going to write the sum of forces in each direction, and that will be the net force. So the net force just means the sum of all the forces in each individual direction. So I'll show you how to do this. Let's say that we have a problem that looks like this, with some forces in the perfectly horizontal and vertical direction and others that have certain angles to them. So we want to know what is the total net force in the x direction and the total net force in the y direction. To do that, I'm going to start by taking the x and y component of each individual force that has an angle, and this will help me sort that force into the two parts of my table. What part of this force is contributing to the y and what part is contributing to the x. So now I'm going to look at just the x components, just the things that are happening in the horizontal direction, and I can see here I have an 8.7 and a 3 pointing to the right and a 6.4 pointing to the left. Usually when I do this, I call right positive and left negative, so I'm going to record those two numbers to the right as positive and the number pointing to the left as negative. And then when I add these three things together, I get a total net force of 5.3 in the x direction. So that means that all the things happening in the x direction are adding together into a single force that has a magnitude of 5.3 newtons to the right. And now if I look at the y direction, I'm going to consider up to be positive, so I'm just going to take everything that's happening in the y and put it on the table. So I have 7 going up, 5 going up, 6.4 going down, so that's negative, and 5 going down, so that's also negative, and this comes out to be 0.6 newtons when I add these forces together. So altogether, there's an upward force, because up is positive, of 0.6 newtons when I add all the things in the y direction together. So that means that all of these forces are behaving like a single x direction force of 5.3 to the right, and a single y direction force of 0.6 up. There will be many times when we know the net force and need to solve for specific forces. Here we're going to pretend we know the net force is 0 in both directions and find relationships between the different variables. So looking at this problem, I can see that I have one force that has an angle, so I'm going to break it down into its x component and its y component, and then look at what's happening in the x direction. So I can see, again, if I'm considering right to be positive, I'm going to record that first number as positive and the force of friction pointing to the left as negative, like that. And in the y direction, I can see I have two forces pointing up, one pointing down, so this is how I'm going to record those. And so now I get from my table, because I know in this specific case that the total net force in both directions is equal to 0, I can solve for new relationships between the variables. So when I rewrite that table, I can see that ft times cosine of theta minus force of friction is equal to 0, and ft sine theta plus the normal force minus the force of gravity is equal to 0. So if I rearrange these a little, I get some identities. I can see that the force of tension times cosine of the angle is equal to the force of friction. So that's an interesting result. That's a way I can solve for one of these missing variables. And the force of tension times sine plus the normal force is equal to the force of gravity. Again, an interesting result. I could use that to solve for some of the variables that I have here. So that's how you solve problems using that force table. For a lot of the problems in this unit, the net force will always equal to 0. So for the most part, you're going to be expected to find missing forces using that force table. This video is going to be about the difference between mass versus weight and how to find weight specifically. So mass is the amount of matter in an object. It's measured in kilograms or kg, and it's a scalar. Weight is the force of gravity acting on an object. It's measured in newtons, and weight is a vector. So I could describe how much physical stuff makes up this apple, and if I were doing that, that would be an example of the mass, how much matter is actually in the apple. The weight of the apple is a measurement of the strength of the force that is pulling it down toward Earth, the force of gravity. So weight and the force of gravity are actually equal to each other. And the equation for a force is equal to mass times acceleration. We're going to talk about that a lot more in the next unit. For now, you just need to know that because the acceleration of gravity is labeled g, the equation for the weight of an object is weight is equal to mass times g, or m times g. So here we can imagine that the apple has a mass of 0.1, and g on Earth, as you know from the previous unit, is always 9.8 meters per second down. So the weight must be 0.98 newtons when I multiply them together. So to find the weight of an object, you just take its mass in kilograms and multiply it by 9.8. If we put this apple into deep space, the mass would actually stay the same. This is something that's a little confusing, but it also helps to illustrate the difference. There wouldn't be any weight because there wouldn't be any force of gravity in space, but there's still a mass. There's still an amount of stuff that makes the apple up, regardless of what forces are acting on it. So the mass here is the same, but the g has gone to 0, so there is no weight. So the weight of an object can change depending on its location, but the mass cannot unless you change what the material is made of. Here, the mass on the moon is still 0.1 kilograms. That's going to be the same. G on the moon is only 1.6 rather than 9.8. So the weight of this apple on the moon is going to be 0.1 times 1.6, which is just 0.16 Newton. So that's about a sixth of what it was on the Earth. If you want to try them out, these are some practice problems that you can do just to challenge yourself, finding the mass and weight of a person with a mass of 60 kilograms on each individual planet. So to find those different weights, you can just use G on each different planet. I've listed them up there. If you want, you can pause the video now, and I'll give you the answers in just a moment. Okay, here they are. Notice that the mass stays the same regardless of what planet you're on, and the weight is determined by the mass times the acceleration of gravity on that specific planet. So this is a summary, and that's all that you need to know. This video is going to be about the difference between static and kinetic friction. So friction is a force that acts against an object's motion. It's created by the object interacting with the surface it is on, and the force of friction always acts parallel to the surface and against the motion of the object. So whether that object is standing still and the friction is preventing it from moving forward, or if it's moving, that friction is still pushing against its motion or potential motion. Friction depends on the normal force acting on the object from the surface and the material the surface and object are made of. We're going to talk about that in more detail today. We haven't so far. In this video, I'm going to give you an equation that relates these things. So the bigger the normal force on the object, the bigger the force of friction can be. So that basically means that the more force the surface has to push up on the object with, the more friction it's going to experience as a result. So this introduces a new idea called the coefficient of friction. Coefficient of friction is the ratio of the force of friction to the normal force. The coefficient of friction depends on the materials the surface and object are made of. Bigger coefficient of friction means a bigger force of friction between that object and the surface. The symbol for the coefficient of friction is mu. That's a Greek letter. It basically looks like a U with a long tail on the left, and it's pronounced mu. And it doesn't have any units associated with it because it's a coefficient. Another way you can understand that is that it's equal to a force divided by the force, so the Newton's unit would cancel out and leave you with nothing. If I rearrange this equation, it comes out to be this, and we're going to talk about it in this form a little bit more. Coefficient times the normal force is going to be equal to a force of friction. So the idea here is that because the normal force between an object and a surface doesn't necessarily have to change, if the coefficient is very small, that means that the force of friction is going to be very small. So something like a person standing on snow or ice, that situation has a very low coefficient of friction. So the frictional force is very small, so any downward force is going to have a pretty easy time accelerating that person in the downward direction. If we make the coefficient of friction very large, the force of friction is going to be very large. And so if you're just standing on the road, the force of friction is enough to hold you back from accelerating forward in a downward direction. Like if this person's standing on a hill, we can imagine that that force of friction is enough to keep them from starting to slide down the hill, because here the coefficient is very large. So now I'm going to talk about the two types of friction. The first type of friction is called static friction. This is the force of friction that prevents an object from moving. It perfectly balances other forces parallel to the surface of the object, as long as those forces are below a certain maximum. To find the maximum static friction from a surface, you're going to multiply the coefficient of static friction on the surface by the normal force on the object. So let's do a calculation with this box here. I can see that the downward force of gravity would be 1,960 newtons, so that means the normal force is also that. And I'm going to pretend that the coefficient of static friction between the box and the concrete is 0.62. So I'm going to write this equation. So what this is telling me is that the force of static friction is always going to be less than or equal to 0.62 times 1,960, which is equal to 1,215.2 newtons. So what this is telling me is that this is the maximum amount that the static friction can push back on the box before the box begins to move. So if you only push with 200 newtons, it's very easy for the static friction to push with 200 newtons back and prevent the box from moving, because that's below the 1,215 mark. That's below the largest possible static friction. If you push with more force, the friction is still able to perfectly balance you out as long as it's below that maximum. Once you push with anything greater than the maximum force of static friction, the force of static friction in return is only able to be that smaller number. And because the number pushing to the right is bigger than the number pushing to the left, the object is going to begin to accelerate in that direction. And once it starts to accelerate, static friction no longer applies because we are now moving. and now a different type of friction is going to take over. The second type of friction is called kinetic friction. This is the force on a moving object. It always points opposite the object's velocity, and it does not depend on any other force on the object besides the normal force. So just like the static friction, there's a similar equation for the kinetic friction. Force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. Okay, let's do an example here. Here for this box, I'm going to pretend that the coefficient of kinetic friction is 0.5. So for this box, because the normal is 1,960, the force of kinetic friction is 0.5 times 1,960 newtons, which is equal to 980 newtons. So if you push along with 980 newtons and it pushes back, there's not going to be any acceleration on the object. It's just going to go at a constant rate because all the forces are balanced out. If you push with a greater force than the force of kinetic friction, the force of kinetic friction doesn't really care. It's not going to adjust itself at all. It's just always equal to that one number. So here the acceleration would exist. The object would get faster and faster and faster because there's an unbalanced force there. And if the force from your push is less than the force of kinetic friction, that means that over time the object is actually going to slow to a stop because the force of friction is pushing it back in that other direction, so the acceleration would be negative. Kind of a random fact, the relationship between the static and kinetic friction, the coefficient of static friction is always greater than the coefficient of kinetic friction for any surface. So just to summarize how static and kinetic friction work, to start an object moving, a force greater than the static friction needs to be applied. To keep the object moving, a force greater than or equal to the kinetic needs to be applied. The coefficient of static friction is always greater than the coefficient of kinetic friction. So watching the animation here, we can imagine we're trying to make this box move, and we start to push on it, and as we push on it, there's a force of static friction that's always pushing straight back, canceling out that force. But there's a maximum amount of static friction that can push back, and if we equal that or go any farther, the object will begin to move, and it's replaced with the force of kinetic friction, which is a little bit smaller than the force of static friction. This is a conclusion. This is all you need to know about the two concepts. You can copy this down if you would like. Otherwise, you can start doing the problems. This video is going to be about Newton's first law of motion. There are three altogether. This unit's going to cover the first and the third. You've probably heard Newton's first law expressed before. It's normally said something like, an object at rest will remain at rest unless acted on by a force, and an object in motion will remain in motion unless acted on by a force. But I don't think this really clarifies exactly what the law is talking about, so I'm going to restate it. I'm going to say it like this. If the net force on an object is 0 on an axis, the acceleration is also 0 on that axis, and vice versa. And if there's a non-zero net force on an axis, there's a non-zero acceleration on that axis, and vice versa. So I'm going to talk a little bit more about what that means. Looking at this first example here, we have an apple sitting on a table, and we can see that it doesn't have any acceleration in the x direction or in the y direction. Its x and y velocities are not changing, they're both remaining at 0. So if there's no acceleration on an axis, Newton's first law tells us that the net force on that axis is 0. So I'm going to take that information and put that into my force table and say, therefore, the sum of the forces in the x direction must equal 0 because of Newton's first law. If there's no acceleration, there's no net force, and if there's no net force, there's no acceleration. And there's no acceleration in the y direction. It's not getting any faster or slower in the up-down direction. So that means that the net force in the y direction is also 0. So that's how we use Newton's first law to solve problems. And now that I have this information, I can use it to derive other interesting information. So here I can see that the only forces acting on the apple are the force of gravity pointing down and the normal pointing up. So I put those into my table and find that they must be equal to each other. And the way that I know that is really through Newton's first law. Without that, I wouldn't have known that the net force is equal to 0. Here's another example. Let's say that this object is not moving. If it's not moving, there's no acceleration in the x or y direction, so we can put 0 newtons as the net force and use those 0 newtons to come up with identities between these variables, between the forces, and solve for interesting new pieces of information about the forces, like this. So the way that we get that information that the net force is equal to 0 is through Newton's first law: no acceleration, no net force, no acceleration. Let's look at another example. Here a car is driving at 65 miles per hour on the highway. And so we can ask, is this car accelerating? And it's definitely not accelerating in the y direction. It's not going up or down at all, so its y velocity is staying at 0. But it's actually not accelerating in the x direction either, because it's maintaining a constant velocity of 65 miles per hour. And acceleration is a change in velocity over time. So if the velocity is not changing, if it's staying at 65 miles per hour, that means that there's no acceleration. So that means that all the forces on this object must also balance out to make 0 in both directions. That can tell us something interesting as well. So to maintain that 65 miles per hour, obviously the normal force from the ground needs to balance out with the force of gravity. We can also see that the forward applied force from the car's engine has to balance out whatever force is pushing back against it, which in this case would just be air resistance. So this is saying that to keep a car moving at that rate, to keep it moving at 65 miles per hour, you don't have to apply some crazy force on it. You just have to balance out the air resistance. If you drive, you may have noticed that when you're on the highway, you don't have to keep your foot on the gas pedal and keep it floored the whole time to keep it at 65 miles per hour. You just need to keep it pressed down a little bit, enough to balance out the forces pushing against the car, in this case the force of air resistance. So this is a misconception that Newton's first law is made to address, and the correction to that misconception. So the misconception is that in all our everyday experiences, we need to apply force to keep objects moving, so we assume that without a force, objects naturally come to rest. So that's the misconception. Objects naturally come to rest if we're not pushing on them. So if this person pushes this box, it seems to naturally come to rest on its own. The correction here is Newton's first law tells us that if an object is slowing down, there must be a non-zero net force slowing it. If there were no forces acting on an object, it would keep its same velocity forever. So the reason why this box slows down is not because objects naturally come to rest. Newton's first law tells us that with no forces acting on them, they actually keep going and going and going forever. So the reason why this box is slowing down is because there must be some non-zero net force accelerating it. In this case, that would be the force of friction pushing back against the motion. For examples of objects that don't have any external forces on them to slow them down, a really common example is the Earth spinning on its axis. There aren't any forces on Earth that would cause it to slow down or speed up in its turning, and so because there are no forces acting on it, it just continues to spin that way forever. There's nothing pushing it around. There's nothing keeping it moving except its tendency to continue to move because of Newton's first law. So nothing keeping it moving. The only reason why it continues to turn is because there's nothing to slow it down and stop it. This leads into an important definition, the idea of inertia. Inertia means an object's tendency to keep its same velocity unless acted on by a force. So that's just a description of how objects always want to keep their same velocity and will do so unless we put a force on them. So inertia itself is not a force. That's a very common misconception. Watch out for that. Inertia is not a force. It's just a property of matter that means the matter keeps its same velocity unless you push or pull on it. Objects with more mass have more inertia because it takes more force to change their velocity by the same amount as smaller objects. Newton's first law is often called the law of inertia because it describes objects' tendencies to stay moving at constant velocities. So that's what you need to know about Newton's first law. Most of the teaching that happens with Newton's first law stuff happens through addressing misconceptions, because Newton's first law does break some of our conceptions about the world that we're going to need to address going forward. This video is going to be about Newton's second law of motion. Newton's second law says that the net force on an object is equal to the mass of the object multiplied by the acceleration that the force creates. The acceleration always points in the same direction as the net force. So that means that I can rewrite this law sigma F equals ma, the net force equals mass times acceleration, as sigma Fx is equal to max for the x-axis, and sigma Fy equals may for the y direction. So when I construct my force table, I can put max and may into the net force spot to tell me what's going on with the object. Notice that Newton's second law fits what we know from Newton's first law. If the net force is zero, acceleration must be zero, because if the left side of the equation is zero and the mass is some positive number, the acceleration must be zero to cancel that out. And if net force is not zero, acceleration also has to not be zero, and vice versa. So Newton's second law kind of confirms Newton's first law. So for most of the problems that we deal with involving Newton's second law, one axis will have balanced forces, so the net force will be equal to 0 newtons, and the other will have unbalanced forces, so the net force will not be equal to 0, it will be equal to m times a in that direction. So a typical force table could look something like this. We could have m times ax and 0 on the y direction. So most of the objects that we deal with will have a net force in one direction and 0 net force in the other, because they'll be accelerating along one axis but not along the other axis at the same time. But we can also deal with situations where there are both. Here are 3 examples of using Newton's second law. It seems simple, but it can get a little complicated. A person is pushing a 20-kilogram box with 200 newtons of force. If the coefficient of kinetic friction between the box and the ground is 0.5, what is the acceleration of the box? Okay, so to figure out the acceleration, we have to figure out the net force acting on the box. So I'm going to construct a free body diagram. I know that there's a force of gravity pointing down, a normal force pointing up, a force applied from the person, and a force of kinetic friction on the box, because this box is moving. So according to Newton's second law, if this object is accelerating in the x direction, then the sum of all the forces in the x direction must be equal to the object's mass times its acceleration. And there's no acceleration in the y direction. It's not moving up or down at all. So on the y part of the force table, I would fill out 0 newtons. So looking at what's happening in the y direction, I can see I have a normal force up and a force of gravity down. So if I put those into my y components of the table, I can see that those two forces will balance each other out to make 0. And in the x direction, I have a force applied forward and a kinetic friction backwards, so that's how I would write them in my force table. So using my force table, I can now write two equations for the net force in the x and y direction. So I know that this equation must be true and this equation must be true as well. And I can now plug in numbers and see if I can solve for that acceleration. So in the y direction, I can see that the normal force has to be equal to the force of gravity. So when I multiply out the force of gravity, I get 20 times 9.8. So the normal force must be 196 newtons. And I also know that the force of kinetic friction is equal to the coefficient of friction times the normal force. So I multiply that out, and I find that the force of kinetic friction in the x direction is 98 newtons. So I plug that into my equation on the left for the x-axis, and I know that this person is applying 200 newtons, and the force of kinetic friction is 98. So 200 minus 98 must equal the net force, and that's also equal to the mass times the acceleration in the x direction. So I get 102 newtons is equal to the mass times the acceleration, and when I plug in the mass, I find that the acceleration of this box is 5.1 meters per second squared. So that's how you would use Newton's second law to solve a problem for acceleration. And I can see here that because acceleration is positive, it points in the direction that we are calling positive. So I called the person's applied force positive and the friction negative, so the acceleration is pointing in the same direction as the person's push. Here's another example. How much force do you need to pull up on a 10-kilogram grocery bag to make it accelerate up at 2 meters per second squared? There's a very common mistake that happens with lifting problems like this, where students will just take the acceleration, multiply it by the mass, and say that it's the force, because F equals ma. But Newton's second law only works when we're dealing with the net force, not the individual forces on the object. So let's look at the net force. We still have a force of gravity down on this bag and an applied force pulling it up. So when I put this into my table, I know that it's not accelerating in the x direction at all, so the net force there must be 0, but it is accelerating in the y direction, so that's going to be equal to m times ay. And I'm going to call up positive here, so I'm going to say that the force applied is positive and the gravity is negative. So this is the equation that I get out of that. Fa minus Fg is equal to m times a in the y direction. And when I plug this in for my force of gravity, I know that the mass is 10, so 10 times 9.8 is the force of gravity, and I know that my mass is 10, and my acceleration is going to be positive 2, because I'm considering up to be positive. So I plug that into m times a, and this is what I get. Fa minus 98 newtons equals 20 newtons. So that means that Fa, the applied force, must be equal to 118 newtons. So if you want to make a 10-kilogram bag accelerate up at 2 meters per second squared, you need to apply a force of exactly 118 newtons on it to do that, according to Newton's second law. Here's one more example. We're going to be working with this concept a little bit later in class, but you may have noticed that Newton's second law ties most of the material that we've been talking about in class together. It connects the Unit 4 materials on forces with the Unit 3 materials on acceleration. So here's an example of using both of those ideas at the same time. So what force do a 1,000-kilogram car's brakes need to create to slow the car from 30 meters per second to a stop in 50 meters? Assume no air resistance. So let's try to figure this out. We know that if the car is slowing to a stop, the acceleration is going to be pointing in the opposite direction of the velocity, because it's taking away from the velocity. So turning this into a free body diagram, these are the forces that I have on the car. There's a normal force going up, a force of gravity down, and a force of kinetic friction going to the left from the brakes. So I'm going to plug these into my force table, and I know that the car is not accelerating in the up-down direction, but it is negatively accelerating in the x direction. So I'm going to say negative Fkf is equal to max. So my issue right now is that I have no way of getting to the force of kinetic friction from this problem without knowing the acceleration. But I'm actually given enough values to solve for the acceleration because I have 3 of the kinematic variables. I specifically have the starting velocity of 30 meters per second. Because it's coming to a stop, that means that the final velocity is going to be 0 meters per second. And it's taking 50 meters to do that, so the displacement is 50. So I can use 3 of the 4 kinematics variables to solve for the 4th. So I'm going to solve for acceleration. And looking at my kinematics table, I can see that I'm going to use the 3rd equation because that's the only one that has all 4 of my values. So I'm just going to start plugging these in. And I find that the acceleration should be negative 9 meters per second squared. Notice that I kept the directions consistent with the directions that I defined on my free body diagram. So I'm considering left to be negative here because the force of kinetic friction is negative. So that means that because it's moving to the right, the starting velocity has to be positive, and its displacement also has to be positive because it's still being displaced to the right. So that's going to be really important when you solve these problems. You have to keep left and right consistent. If one thing is positive, the other thing has to be negative. So this is going to be a negative acceleration. Okay, now I can just take this and plug this in and figure out what the force of kinetic friction is on its own. So I have the acceleration, I have the mass, and I know that those two together are going to equal the force of kinetic friction because that's the only thing happening in the x direction. So I find that the force of kinetic friction, the magnitude of that force is equal to 9,000 newtons, and it's going to be pointing to the left. The negative canceled out there, that was a little strange. If I put the negative sign next to the symbols itself, then the symbols themselves just stand for the magnitudes of the force, so I know that this force has a magnitude of 9,000 newtons pointing left. So that is how you use Newton's second law. They're going to be more complicated problems in class, but those complications don't come from Newton's second law. They come from incorporating previous knowledge with Newton's second law. So ramp problems, calculating friction, Newton's first and third law, stuff like that. All of these are going to come up and affect Newton's second law problems in some way, and as long as you can incorporate the information from that, you'll be good. This video is going to be about Newton's third law and action-reaction pairs. Before we start on Newton's third law, I just need to show you something about force notation. So forces always act on an object and are created by a second object. To show which force is being referred to, we write two letters or numbers or symbols next to the letter F. The first symbol shows which object is being acted on, and the second symbol shows where the force is coming from. So this is a way of saying the force that exists on object 2 from object 1. So if I were talking about this force, I would say this is the force on the box from the person, so I would write this as F box person, like that. And the force pushing back on the person, I could call F person box, like that. Here we have gravity acting on the bird, and because gravity is created by the Earth, I would say this is F bird Earth. So now that you have this notation, you're ready to talk about Newton's third law of motion. Newton's third law, in the everyday phrasing, says for every action there is an equal and opposite reaction. But that alone doesn't really tell you very much, and a lot of people misuse that to say a bunch of different stuff. Like they might say, oh, for every action there's an equal and opposite reaction. That means that if the stock market's up one day, it's going to be down the next. If one party takes control of Congress, the other party will in the next election, so on and so on. And that's not what it means at all. It means something extremely specific about force. So I've rephrased it in the black letters up there to be more clear. So the rephrased version of Newton's third law is if object 1 puts a force on object 2 puts a force with an equal magnitude and an opposite direction on object 1 always. So another way of saying this, to write it using our notation, is to say that the force on object 2 from object 1 is exactly equal to the force on object 1 from object 2. Those two react to each other and create each other. This is a little counterintuitive because we can imagine, for example, a bug hitting a truck. And our intuition is that because the bug is so much more affected by the collision, the truck must put a much larger force on the bug than the bug does on the truck. But according to Newton's third law, whatever force the bug puts on the truck is exactly equal to the force that the truck puts on the bug. So how can this be? The reason why is if I change these to the mass of the bug and the mass of the truck, one mass is very big and the other is very small. So to keep those two forces equal, we're also going to have to change the accelerations. So if the mass of the bug is very small, it's going to have a very large acceleration if it's experiencing the same force. And if the mass of the truck is very big, it's going to experience a very small acceleration from the same force. As the mass gets bigger, the acceleration gets smaller if we're keeping the force the same. So the truck is accelerated much less than the bug, and that's why it seems to be affected and is affected much less by the same force. It's because it has a larger mass, not because the forces are different. The forces between those two objects are the same. So larger objects do not put larger forces on smaller objects. They are always the same. If this 10 kilogram object puts 20 newtons on the 5 kilogram object, the 5 kilogram object puts 20 newtons right back on the 10 kilogram object. And you may have heard me reference before that force is equal to mass times acceleration. So if we do some math there, we can find that the acceleration on the 5 kilogram object is 4 and the acceleration on the 10 is -2. So the acceleration on the smaller object is bigger than the acceleration on the larger object, but they're both the same force. That's what Newton's third law is telling you. A very common misconception about Newton's third law is that these balanced force pairs, these pairs of forces that are created by each other, exist on single objects. Like you can use a single free body diagram and say, oh, if there's a push to the right, there's also a push to the left on the same object. But that is absolutely not correct. That is not the correct way of understanding this. Newton's third law is the only one of Newton's laws that is talking about two different objects and a force that exists on both. So this is what an action-reaction pair would look like. If these two boxes were putting a force on each other in these directions, these two forces would be the action-reaction pair. But if you only looked at one of the free body diagrams, you would only notice one of the two forces. So when finding action-reaction pairs between two forces, those are always going to exist between two objects, not just one. So an action-reaction pair is a set of two equal and opposite forces that are created by two objects interacting with each other. So we normally write the pair as x pushes on y pushes on x. So here are a few different examples of action-reaction pairs in this picture. A person pushes on a box, the box pushes back on the person with the same force. The apple pushes on the box pushes on the apple, so the apple is pushing down on the box pushes back up on the apple. The person pushes on the ground pushes on the person. The box pushes on the ground pushes on the box. And for the force of gravity, this one's actually pretty interesting. If the Earth is pulling down on the person with the force of gravity, that means that the person is actually pulling the Earth up with the force of gravity. All objects with mass attract each other with the force of gravity. So all of these masses in this problem are actually attracting the planet Earth to them. So the reason why the Earth isn't immediately pulled up to the point of the objects is that the Earth is so massive that its acceleration is almost zero. It's almost nothing. Earth's mass is something like 10 to the 24th kilogram, so it takes a lot of force to even accelerate it a little bit. And so the forces from these objects obviously can't actually pull the Earth up toward them just because the Earth is so massive, but they are putting that force of gravity on the Earth because all objects with mass attract all other objects with mass with gravity all the time. So this is the conclusion, this is what we went over, and this is the idea of Newton's third law. F on object 2 from object 1 is always equal to F on object 1 from object 2. In this video, I'm going to talk about how to do ramp problems in physics. Ramp problems are very specific free body diagram problems where the object is on some kind of inclined plane. And there's a very specific pattern for doing ramp problems that if you memorize makes everything much easier. So we're going to imagine that we have this object on a ramp with a certain angle. So I'm going to start drawing the forces on this object, imagining that it is not moving. The first force we would have is the force of gravity, which always points straight down. Then the normal force, which always points at a 90-degree angle to the surface. You'll notice that here it's not pointing straight up, it's pointing at a 90-degree angle to the surface that's creating it. And the force of friction must be the third force, which is holding this object up and preventing it from sliding down the ramp. There are no other possibilities for what that force can be in this specific situation. So if I wanted to understand what was going on here, I could break up these forces into x components and y components and try to solve the problem, but that would take a while. There's actually an easier way of doing this. So basically the idea of ramp problems is we're going to rotate the x and y axis. The reason we can do this is that the x and y axis were invented by people, by humans. It's just a system that we impose on the world, and there's no reason why it has to be one particular way. So if I rotate the y-axis and the x-axis to match the normal and the friction force, I now only have one force that has an x component and a y component, and that's the force of gravity. You can see here that this would be its y component because that's how far along it goes along the y-axis, and this would be its x component because this is how far it goes along the x-axis. So now that I have only one force that has an x component and y component, this is going to be much easier for solving the problem. So I can see just looking at these forces that if these are all balanced, if they all add together to make 0, that means that the normal force is going to balance out with the gravity's y component, and the friction is going to balance out with the gravity's x component. So if I can find the x and y component of gravity, then I'm going to know the value of the normal force and the frictional force as well. One last thing you're going to need to know is that the angle between the gravity and that new rotated y-axis is always going to equal the angle of the ramp. I'll include a proof at the end of this video if you don't understand why, but for now I'm just going to leave that angle there. That identity will always be true. So now we can start to solve for missing forces. If I replace gravity as mg, I can see that the y component here is going to be mg cosine theta because that's the side that is adjacent to the angle. And mg sine of theta is going to be equal to the x component on this new axis. So because the normal and the y component are equal, here the normal is going to equal mg cosine theta, and the force of friction is going to equal mg times the sine of theta. This pattern will always hold for ramp problems like this. So as an example, if we have a problem that asks a 10 kilogram box sits on a 30-degree ramp, what force of friction keeps it in place, we can use these identities to figure it out. I can see that the force of gravity is going to be 98.1 newtons. And if I rotate the axes and find these new x and y components, I can say that this angle here is also 30 degrees by the rule that that's the same angle as the ramp itself. And so each of these components are equal to this and this, 98.1 times the cosine of 30 and times the sine of 30. So those are the values of the x and y components along these new rotated axes. And so that is equal to the normal force, and that is equal to the force of friction. So that is my answer. What force of friction keeps it in place? The answer here is 49 newtons. That's what friction has to balance out in the gravity to keep it at 0. Other forces can also take the place of friction. We can imagine that we have tension, a rope holding it up, a spring holding it up, things like that, a person holding it up, but those are always going to be equal to that same mg times sine of the angle. If there are more forces acting on the object, but you know that the object isn't moving or moving at a constant velocity, you'll need to use the rule from Newton's first law that both tilted axes must add together to make zero altogether. So as long as you're using that rule, you'll still be able to add these forces together. Okay, so that's it for the video. I'm just going to include a quick proof that those two angles are equal. So when we look at our force of gravity, it's going straight down, and it intersects with the bottom of this ramp with a 90-degree angle because the bottom is perfectly horizontal. We can also draw the normal force at a perfect 90-degree angle to the ramp because that's what the normal force is. It's a 90-degree force to the surface. And so if that angle is 90 degrees, this angle here is also going to be 90 degrees. So the sum of those two angles that I just drew must be equal to 90. Looking at just this triangle, I can see that if the red angle is theta, the purple angle must be 90 minus theta using triangle geometry because they all have to add up to make 180. So putting this into my identity, replacing it with the purple angle, I can see that theta by itself must be equal to that red side, or the red angle here must be equal to theta. And so that angle is the angle between the new y-axis and the gravity. So that's why that angle is equal to the angle of the ramp, and that will always be true for these types of problems. So that's how you do ramp problems. As usual, the way that you get better is practice.
This is the first in a series of video lectures on momentum. This first lecture is just going to cover the basic definition and equation for momentum. Momentum can be understood as a measurement of how difficult it is to make an object stop. The variable for momentum is lowercase p, and the unit is Newton seconds. I'll explain why that is in just a moment. So in thinking about how difficult it is to make an object stop, there are a few different variables that could affect that difficulty. For example, if we have a truck and a baseball moving at the same velocity, and we think about which one would be more difficult to make stop, which one would require more effort from us to stop, it seems pretty clear that the truck would be more difficult to stop than the ball. And the reason why is that the truck has more mass than the ball. So it seems like if something has more mass, it's probably going to be more difficult to stop. So more mass probably means that the thing has more momentum. We can also imagine two baseballs of the same mass, but one is moving a lot faster than the other. And in this case, the faster ball would probably be more difficult to stop. It would take more effort to stop a very fast-moving ball than a slow-moving ball. So it seems like the more velocity something has, the more momentum it should have as well. And this is reflected in the equation for momentum. Momentum is just equal to mass times velocity. That's all that it is. It's a deceptively simple equation because we can draw a ridiculous amount of new information out of that definition, which we'll go into in future lectures. For now, you just need to know that the momentum p is equal to the mass times the velocity. This explains why the unit is the way that it is. I've left a proof of why the unit is Newton seconds above my head. Basically, the unit of mass is kilograms and the unit of velocity is meters per second. So I can prove from that that the unit could either be kilogram meters per second, which it's sometimes measured in, or it could also be Newton seconds. Those are two different options for recording the momentum of an object. Because momentum has velocity, it's a vector, and if one direction is positive, the other direction is negative. And it's entirely arbitrary which direction I define as positive and negative, just like with all other vectors. I can imagine, for example, that I have a rightward moving baseball and a leftward moving truck, and if I'm calling right positive and left negative, I would apply the positive to the baseball and the negative to the truck's velocity, and when I multiply out the mass and the velocity, I find that the momentum for the baseball is also positive and the momentum for the truck is also negative. So momentum, just like velocity, has a direction. It's a vector. It has a size and a direction. And it's entirely arbitrary which direction I consider to be positive and negative. If I flip the positive and negative, that just means that I have to flip which velocity is positive and negative here, which also flips which momentum is positive and negative. Because momentum is a vector, we can also describe an x direction momentum and a y direction momentum. If I have this 2 kilogram ball moving up at a velocity of 10 meters per second at an upward angle of 30 degrees, using trig, I can find that its x velocity is 8.7 meters per second and its y velocity is 5 meters per second. And if I multiply all of those by the mass, I can get the momentum in each direction as well. So it has an x direction momentum, a y direction momentum, and a total momentum using the same rules for vectors. So that's all you have to know about the basic definition of momentum. The definition itself is pretty simple, but we can do a lot with it. This is the second video in our series on momentum, and this video is going to be on impulse and force time graphs. Impulse is a change in momentum. It's the literal number amount that momentum changes by in an object. It's also equal to the final momentum of an object minus the starting momentum that the object has. And because it's a change in momentum, the variable for impulse is just delta p. Delta, that triangle symbol, just means a change in. That's used a lot in math to mean a change. And the units of impulse are Newton seconds, so just like momentum itself, impulse is also measured in Newton seconds. Usually a change in a variable is measured in the same unit as the variable itself. I'm going to imagine that I have a positive direction to the right and a negative direction to the left, and I have a bowling ball hitting this pin. So if this bowling ball has a starting mass of 5 kilograms and an initial velocity of 5 meters per second, I can see that the momentum that it starts with, p0, is going to equal positive 25 Newton seconds, because it's the mass times the velocity. So when it hits this pin, I'm going to pretend that it leaves the pin traveling at only 3 meters per second. So if it's only traveling at 3 meters per second, and I multiply that out, I find that the final momentum of the ball is 15 Newton seconds. So the impulse is the change in momentum, so if it went from positive 25 down to positive 15, I can see that the change in the momentum is going to be negative 10 Newton seconds. So the impulse on the ball is negative 10 Newton seconds. So that's the meaning of impulse. And impulse, just like everything else with momentum, is dependent on which direction we're considering positive and negative. If I switch this around, so left is considered positive and right is considered negative, that means that both velocities of the ball will be negative, which means that both momentums of the ball will be negative. And if I change the momentums of the ball to be negative, it's going from negative 25 to negative 15. That means that the impulse is now positive 10, because negative 15 minus negative 25 is positive 10. So just like with momentum itself, the sign for impulse, whether it's positive or negative, depends on which direction we're considering to be positive and negative. So impulse also has a direction. The equation for impulse is a little surprising. The equation is actually not just the final momentum minus the initial momentum, it's also equal to the net force on the object multiplied by the time that force is applied. I've left a proof above my head of why that is. I'm also going to prove it to you with the same ball example. So let's say that we have the same bowling ball and it's rolling at 25 Newton seconds, and this time we want to understand how much impulse it feels from this force time equation. So I'm going to imagine that we have a force of negative 5 newtons applying to the ball for 2 seconds. Now, I know that if this is the net force on the ball, net force is equal to mass times acceleration, and I have the mass of the ball, that's 5 kilograms. So if I plug this into F equals ma, negative 5 newtons is equal to ma, so that's equal to 5 kilograms times a. So that means that the acceleration of the ball is negative 1 meters per second squared here, as it's slowed for 2 seconds. Plugging this into a Suvat table, if it starts with a velocity of 5, like it does in this situation, and it's slowed at a rate of 1 meter per second squared for 2 seconds, because that's the total time of the collision, the final velocity of the ball, calculating this out, is going to be 3 meters per second. So if the final velocity of the ball is 3 meters per second, that means that the final momentum of the ball is 15 Newton seconds, because it's the mass multiplied by the velocity. So you'll notice that just by using the properties of the net force and the time and kinematics, I was able to predict the final momentum of the ball without even knowing that impulse equation. So what this new equation is doing is telling us that instead of having to do all that kinematic stuff that I just did, I can just take the net force times the time, and that will be equal to the impulse. So this equation is telling us that the impulse is negative 5 times 2, which is negative 10. So it's telling us that if we apply a force of negative 5 newtons for 2 seconds, the ball is going to change by negative 10 Newton seconds. So if it starts at 25 Newton seconds, it goes down to 15 Newton seconds. So I was able to use that equation just by plugging in force times time without having to bother with the kinematics. So this is kind of a shortcut to understanding the final velocity and final momentum of an object. So this same impulse can occur with different forces in different times. This could have also occurred with a force of negative 10 newtons for 1 second. And if you plug that back into the kinematics, you'll actually find that that still predicts the final velocity to be 3 meters per second. And if you plug in 1 newton of force and a time of 10 seconds, that will also predict a final velocity of 3 for a total impulse of negative 10. So I can just keep replacing these values, and all these different values come up with the same impulse. So multiple forces and multiple times can combine to make the same total impulse. Impulse was actually how Newton originally wrote his second law of motion. He actually originally wrote it as force is equal to the change in momentum over time, which is just a rewriting of the equation above. If you multiply that original Newton's second law by the time, you get force times time is equal to the change in momentum. And today we usually write it as F equals ma, but the two statements are actually identical to each other. So that's just an interesting historical fact and another origin of that equation for impulse. I'm going to do a few example problems of calculating impulse. I'm going to start with example problem 1. A 1,000-kilogram car is moving at 30 meters per second, and if its engine puts 5,000 newtons of force forward on the car for 3 seconds, how fast will it be moving at the end? So writing down what we know, I know the mass, the initial velocity, the time, and the net force. And I also know that the impulse is equal to the final momentum minus the original momentum, and it's also equal to the force times the time. I can calculate the original momentum by just multiplying the mass times the velocity, and when I do that, that's equal to 30,000 newton seconds. So plugging in what I know, I find that the final momentum minus 30,000 newton seconds is equal to 5,000 newtons times 3 seconds. So doing the math, I find that the final momentum is 35,000 newton seconds. And I know that the final momentum is equal to the mass times the final velocity, so dividing out the mass, I get a final velocity of 35 meters per second. So that's an example of using impulse to solve a problem. Example number 2 says a person on a bike with a total mass of 80 kilograms is moving at 20 meters per second. And if they want to slow to 5 meters per second in 5 seconds, how much force do they need to apply with their brakes? Again, writing down what I know, I have the mass, the initial velocity, the final velocity, and the time. So that actually allows me to calculate the initial momentum and the final momentum just by multiplying the mass by the initial velocity and the final velocity. So plugging this into my impulse equation, I find that 400 newton seconds, the final momentum, minus 1600 newton seconds, the initial momentum, is equal to the net force times 5 seconds. Solving for the net force by itself gets me negative 240 newtons, and it makes sense that it's negative because the brakes would be applying a force in the opposite direction of the positive motion of the bike. So this is another example of using impulse to solve for missing info. I'll give you one more. A 500-kilogram car is driving at 10 meters per second. If its brakes can apply 1,000 newtons of force, how much time will it take to stop? So I know the mass of the car, I know the initial velocity is 10, and I also know the final velocity is 0 because it's trying to come to a stop. And the net force on the car is going to be negative 1,000 newtons because if I'm considering the forward motion to be positive, the brakes are applying a backward force, so I have to consider that backward force to be negative. Plugging this into my impulse equation, I can find that the initial momentum of the car multiplying the mass times the velocity is 5,000 newton seconds, and the final momentum is just 0 because it's at rest. So 0 minus 5,000 newtons is equal to the net force times the time. Solving this out for time, I get that the time is equal to 5 seconds. So if you're driving that car at that rate and you can apply that much force, this is the amount of time that it would take to stop the car. We'll now move on to the second part of this lecture, which is on force time graphs. There's a reason why I have this in here as well. It's related to impulse. A force time graph shows the net force applied on an object on the graph's y-axis and the time that the force is applied for on the x-axis. The area under the curve of a force time graph is equal to the impulse on the object. So the reason why this is the case is that if I draw this line for a constant force applied over a certain amount of time, and then draw the area under the curve, that's just the area between the line and the x-axis. I can see that this is a rectangle with a height that's equal to the total force being applied, like that top number on that green line would be the force applied and the bottom number is 0, so the length of that green line is just the total force applied, and the width of the rectangle is just the total time that has passed. So because the area is the height times the width, here it's going to be the force times the time, which we know is equal to the change in momentum, which is equal to the impulse. These can look a little complicated, but it never gets much more complicated than solving for triangles and rectangles. So here, if I wanted to know the total change in momentum of this object as this non-constant force is applied to it, I just have to find the total area under the curve. So this is a right triangle, so that's easy to calculate. It's just 1/2 base times height, so I can see that that would be 10 newton seconds, 1/2 times 5 times 4. And then the area of this rectangle would be equal to 25, so that's an additional 25 newton seconds of impulse. And then this shaded region would be plus 10. And then anything under the x-axis is considered negative, and I'm going to draw that between the line and the x-axis still. So this is what that final area would look like, but this is adding a negative impulse to the object.
So that last one would actually be equal to -6 because it's 3 times -4 times 1/2. Adding all those areas together gets me a total impulse of 39 newton seconds on the object. Here's an example problem where this would come up. A person in a 1,000-kilogram car presses on the gas pedal more and more and uniformly increases the force of the engine on the car from 0 newtons to 2,000 newtons over 8 seconds. If the car has a velocity of 12 meters per second to start, how fast will it be going after those 8 seconds? So I'm going to use the fact that the total change in momentum is the final minus the initial, and I know that the initial momentum is the mass times the initial velocity, which is equal to 12,000 newtons. And I know from the problem that the car is applying a force starting at 0 and going to 2,000 over 8 seconds. So this is what the force time graph would look like. And so the area under that curve is going to be equal to 8,000 when I multiply that out, because it's just 1/2 base times height, so 1/2 times the base of 8 times the height of 2,000 gets me 8,000 as a result. So the impulse is equal to the final minus the initial momentum, so that's going to be 8,000 is equal to the final minus 12,000 newton seconds. So solving that, the final momentum of this object is going to be 20,000 newton seconds, so that's the final momentum of the car, and solving for the velocity using momentum is equal to mass times velocity gets me a final velocity of 20 meters per second. So this is actually something that we weren't able to do before in class. Before, we could only deal with constant forces in equation, forces that weren't really changing. We couldn't really do any math with constantly changing forces, but now we can have a force that is constantly changing and still predict the motion of the object using the force time graph and our new definition of impulse. This is the third video in our series on momentum. This video is going to cover conservation, which is one of the most important conceptual tools in all of physics. The more you advance in physics, the more central conservation becomes as a concept. So in all physics classes, either momentum or energy is kind of the bridge to your understanding of conservation. So in this class, we're going to start with talking about conservation in terms of momentum, and then move on to talking about it in terms of energy as well. So to illustrate how conservation works, I'm going to start using rules and concepts that you already know to build you up to some new information. Let's imagine that we have a collision between object 1 and object 2 moving in opposite directions. I know based on Newton's third law that when object 1 puts a force on object 2 puts the exact same magnitude of force back on object 1 in the opposite direction. This is always true for every single collision based on Newton's third law. And I also know that the time that the collision takes is the same for both objects. That's kind of just intuitive. If two objects are both in a collision, the collision can't possibly take longer for one object than it does for the other object. So I can see based on Newton's third law that when any two objects put a force on each other, that force is always going to have the exact same magnitude and opposite direction. And based on this intuition about time, those two forces are also going to apply to each object for the same amount of time. So that means that if the forces objects put on each other are always the same, and the time that it takes to apply that force is always the same, that means that the force times the time on one is equal to the negative force times the time on the other. One is just the negative version of the other, but they have the same magnitude because it's the same size of force and it's the same time. So that means, based on our definition of impulse, that whenever one object creates an impulse on a second, the second object always creates the exact same impulse but in the opposite direction on the first object. So this always has to be true. Whenever one object experiences impulse, the other object always has to experience the exact same amount of impulse but in the opposite direction. So that's an interesting concept, and we can draw out a little more info from that idea. Just as an example of what this would look like, let's say that we have two objects moving toward each other with -10 newton seconds. I'm considering right to be negative and left to be positive, and 20 newton seconds like this. And I'm going to use a new concept up in the proofs box. I'm now considering the total momentum of the system. I want you to observe something about the total momentum of the two objects added together. So I can see that I'm starting with a momentum of -10 and a momentum of +20. So that means that the total momentum between these two blocks, if I add both of those together, is going to be 10 newton seconds of momentum, -10 plus +20. I'm now going to imagine that object 1 experiences an impulse of 30 newtons to the left, and I'm considering left to be positive, so that's a positive impulse. So based on the idea that I just showed you in the previous slides, if that object 1 is experiencing a leftward impulse of 30 newton seconds, that means that object 2 is experiencing a rightward impulse of 30 newton seconds. So I'll consider that negative. So remembering now that impulse is not just the force times the time, it's also equal to the change in momentum on the object. So this means that object 1's momentum is changing by positive 30 newton seconds, and object 2's momentum is changing by negative 30 newton seconds. So when I add these two changes to the two objects, I get a final momentum of 20 newton seconds on object 1 and a final momentum of negative 10 newton seconds on object 2. I added 30 to object 1 and I took away 30 on object 2. So you'll notice that the two individual objects now have new individual momentums. But if we consider the total momentum between them, like the total momentum in this system, I added 30 newton seconds on one side, but I subtracted it on the other side. So that means that the total momentum didn't change in that situation. And I can see that it didn't. The total momentum is still positive 10. The individual momentums of the objects changed, but the total remained the same. It stayed at positive 10. This rule about the total momentum staying the same whenever two objects put a force on each other can actually never ever be broken. You'll notice that no matter what impulse I choose to put on object 1, object 2 is always going to experience that same impulse but in the opposite direction, so it'll be negative. So whatever I add to object 1, I have to take away from object 2. And if I plug both of those into my equation for the total momentum, they're both canceled out. And so the total momentum is always going to remain at that same total amount that it started with, as long as those two objects are the only things putting forces on each other. So this leads to a new definition. This is the law of conservation of momentum. The law of conservation of momentum says that when two objects put forces on each other, the individual momentums of the objects change, but the total momentum of the two objects stays the same. This happens every single time two objects interact with each other. The two individual momentums of the objects can change, but their sum, the two momentums added together, stays exactly the same. And the implication of this is that momentum can never possibly be created or destroyed. Momentum can never come into or leave the universe as a whole. It can only be moved around from one object to another object. One implication of this, which is pretty crazy, is that the universe has never gained or lost any momentum ever. The total momentum in the universe added together, if you were to add together every single mass times velocity of every single particle in the universe, that total momentum would be some constant, which is pretty incredible to think about. The momentum can't possibly be gained or lost in any way. So this seems like it would probably have a lot of predictive power for understanding how objects are going to move in the future if this value isn't changing. And that's true, it does have a ton of predictive power. The reason why we care so much about conservation is that using this idea that the total stays the same, we can predict a lot of new information about objects that are interacting with each other. In general, a quantity that is conserved can never be created or destroyed, only transferred or transformed into another type of that same quantity. There are a few different things that are conserved in physics. Things like momentum, energy, mass, and electric charge are all conserved. So none of these things can ever be created or destroyed, only transferred or transformed. Just as an example of what this looks like in problem solving, we can imagine that we have two carts moving in the same direction, but the cart number 1, object 1, has more momentum than object 2. I'm going to use this graph above my head to say that object 1 has 8 newton seconds of momentum, and object 2 has 4 newton seconds of momentum, so the total is going to be 12. We can now imagine that they have some impact at some point, so object 1 impacts object 2 and puts some impulse on it. So whatever impulse object 1 gives to object 2 gives back to object 1, but in the opposite direction. So object 2 is going to gain that rightward momentum, whereas object 1 is going to lose that rightward momentum or gain leftward momentum. So basically, looking up at my graph, that's basically object 1 giving a chunk of its momentum, this change in momentum, over to object 2. So when that happens, the total remains the same. The total amount of momentum that the two carts have has stayed exactly the same. It's remained at 12. But now cart 2 has more momentum than it had before, and cart 1 has less momentum than it had before. So they might move off like this. We can now do some examples with actual numbers. For example, a 5 kilogram cart moving at 5 meters per second to the right hits a 2 kilogram cart moving at 2 meters per second to the left. After they collide, the 5 kilogram cart is now moving at 1 meter per second to the right. What is the new velocity after the collision of the 2 kilogram cart after the collision? So I'm going to start by defining directions. I'm going to say right is positive and left is negative. And when these two carts collide, the total momentum in the system is the momentum of the cart moving to the right, which is its mass times its velocity, which is 5 times 5, plus the momentum of the cart moving to the left, which is its mass, 2 kilograms, times its velocity, which is negative 2 meters per second, because it's moving in the negative direction. And when I add these together, I get a total momentum of positive 21 newton seconds. That's how much total momentum is in this system. So the problem says that after they collide, the 5 kilogram cart is now moving at 1 meter per second to the right, and we want to know the velocity of the 2 kilogram cart. So plugging this in, adding those two new momentums together, I know that the total momentum is going to stay the same. So the momentums of these two carts added together is going to equal 21 newton seconds. So the new momentum of the 5 kilogram cart is 5 kilograms times positive 1 meters per second, and the new momentum of the 2 kilogram cart is 2 kilograms times that new velocity that we're solving for. And now I can just use algebra to solve for velocity by itself, and I get 8 meters per second. So that means that after these two carts collide, it's 100% certain that if the 5 kilogram cart is moving at 1 meter per second, the 2 kilogram cart is going to be moving at 8 meters per second like this after the collision. So we're 100% certain of that based on the laws of physics that we know already. Here's one more example of conservation. We can now imagine that a 5 kilogram cart is moving at 2 meters per second when we drop a 15 kilogram mass onto it, and how fast will it be moving after the mass sticks to the cart? So as this is moving, it starts off with a total momentum of 5 kilograms times 2 meters per second. There's no additional momentum in the system right now. It's just the cart moving to the right. We're now going to imagine that we drop a box onto it that's 15 kilograms. And you'll notice that when the 15 kilograms hits the cart, something kind of weird happens, where because the downward force of the box is balanced out by the upward force of the floor on the cart, the total impulse on the cart, the total change in momentum that the cart experiences is actually going to be 0, because there's no net force on the cart, which means that there's no impulse on the cart. So this means that the total momentum of this cart with the new mass on top is going to be the same that it was before. But now this cart has a total mass of 20 kilograms because it's the 5 kilograms plus the additional 15 kilogram box. So the total momentum that the cart has is now 20 kilograms times its new velocity. So using algebra, I can solve for that new velocity of the cart, and when I plug in those numbers, I find that the new velocity of the cart with the box on top is equal to 0.5 meters per second. So those are two examples of using conservation to solve problems. You're going to see this come up a lot more and a lot more in future videos, but it was important to get through the basic idea of conservation, why we know that things are conserved, and some basic examples of how it's used to solve problems. During the last video in this series on momentum, where I talked about conservation, you may have been watching and thinking that there are very clear examples of when momentum is very clearly not conserved. I was giving a bunch of examples of cars bumping into each other and bouncing off each other, but there are a bunch of examples where it seems like one object begins to move in an interaction and the other one doesn't change its velocity at all. As one example, you could be standing at a table with a cart and put a force on the cart, and because of Newton's third law, the cart puts a force back on you, but it seems like it's only the cart that experiences a change in momentum, because it's the only thing that changes its velocity. You do not change your velocity in that interaction. So because of that, it seems like the cart's momentum changes, whereas yours does not, so the total momentum is not staying the same. There's more momentum than there was before. But this actually isn't true. This is actually still an example of conservation of momentum, and I'm going to show you why. So the cart puts a force on you, but you don't move. So what that means is that there must be something else putting a force on you in the opposite direction, preventing you from moving. And you might remember that in this situation, that force is friction. So friction is keeping you stuck to the ground, preventing you from sliding away when you put a force on something else. But if the ground is putting a force on you with friction, that means that you are also putting a force on the ground with friction in the opposite direction, which kind of makes sense. If you're being pushed back by the cart and the ground has to catch you to prevent you from moving, the ground itself might feel a pull to the left as a result of having to stop you from moving.
So there's a force on the ground. And the ground is connected to whatever building you happen to be in, and the building is connected to the entire Earth. So because the ground is feeling this force of friction from you, the entire Earth, the entire planet, is technically feeling the same force of friction from you. And therefore, because there's nothing to prevent the Earth from moving one way or the other as a result of the force, the Earth is also experiencing an impulse in the opposite direction. So when you push that cart forward, you're actually delivering as much impulse on the Earth to the left as you are to the cart on the right. It's the same impulse. The reason why the Earth is so much less affected is because its momentum is already so gigantic. I did a calculation and I found that Earth's momentum is about 1.9 times 10 to the 29th Newton seconds. The Earth is so big that a small impulse, like the impulse that a cart receives, would barely affect its velocity at all. So that means that we can't understand the change in velocity of Earth, and there's no way we could possibly measure that. It's just too small on such a big planet to really have any way of ever measuring that. So this shows us something interesting. This shows us that if Earth is a part of our momentum problem, if it's one of the objects affected in a collision, we can't solve the problem. We can't find missing information using conservation, and this is not because momentum is not being conserved. It is definitely still being conserved. The reason why we can't solve the problem is only because we can't really know anything about how Earth's velocity changes as the result of very small interactions. So if Earth's a part of our momentum problem, we can't solve the problem. This leads to another question. Isn't Earth always a part of our momentum problems because Earth always puts the force of gravity on objects? The answer here is no, it's not. The reason why this isn't true is because when Earth puts the force of gravity down on an object, it's also pulled up by that object by Newton's third law. So when Earth pulls down on something with gravity, that something also pulls up on Earth with gravity. But the Earth is also normally applying a normal force up on the object, and by Newton's third law, that means that the object is also applying a normal force down on the Earth. So in situations where the gravity balances out the normal force, the Earth is normally not a part of our problem. So we can do math and do conservation problems with objects where the force of gravity and the normal force are being balanced out, and therefore the total impulse on the object from Earth is 0. This is a situation where the total impulse on the object from the Earth is 0, so as a result, the total impulse from the object on the Earth will also be 0, so we don't have to worry about that gigantic mass. I'll give you a few examples and ask whether Earth feels an impulse in each specific example. My first example is pretty simple. It's just two carts moving horizontally and bumping into each other. And you can see that when they do this, the force of gravity and the normal are balancing each other out. So the only forces on these carts are coming from each other. And therefore, if the forces are only applying on each other, the change in momentum is only occurring between those two carts. The Earth is not involved in that impulse. So that means that Earth is not feeling an impulse here, so we can use the conservation of momentum. So if I were to make a graph of the momentum of each cart before and after the situation, one momentum might start negative and the other might start positive, and afterwards they might switch like this, but it's a normal everyday amount of momentum. It doesn't involve the momentum of the Earth, and so I can do regular calculations with it. Here's another example. We can imagine a cart hitting a wall, and we can decide whether Earth is experiencing an impulse from this. And I can see that the wall is applying a force on the cart, and as a result, the cart is applying a force on the wall. And if that's happening, the wall is connected to the building it's in, which is connected to the ground, which is connected to the Earth. So the Earth does experience a force from that. So therefore, it also experiences an impulse. So that makes the total amount of momentum in the problem so large that we can't possibly do any math with it. So here, Earth does receive an impulse, so we can't calculate the total momentum between the objects. So we can't use our regular ideas of conservation to find missing variables. So if the cart is this negative momentum, the Earth would be this impossibly large positive momentum, and I can't really do any math with that to find how the momentum changed. Here's another example. We can imagine a box sliding across the ground with friction, and here, because the ground is putting a force of friction on the box is putting a force of friction back on the ground, and the ground is connected to the Earth, so the Earth feels that same force, so it experiences an impulse. So again, we can't calculate the total momentum because the Earth just has way too much momentum to start off. One last example, we can look at two ice skaters as they push apart from each other, and I can see that the force of gravity and normal force are balanced out, and my only two objects in this problem, the two ice skaters, are only putting forces on each other, so they're the two objects experiencing the impulse, not the Earth. So we could use conservation of momentum to solve that problem.
These examples were meant to build you up to the idea of a system and the idea of an open and closed system. That's the theme of this lecture. I'm going to start by defining what a system is. A system is just a group of objects. That's literally all that it is. So if I circle this box and I say this cart is in my system, this would be the cart system. And I can expand my system and say, okay, this apple is in the system now. I can just decide for myself what objects are in the system. It's entirely subjective and based on what we want to examine. So now this is the cart apple system, and now this is the cart apple earth system, and now this is the cart apple earth bird system. So what a system is incredibly simple. It's just whatever group of objects you happen to want to examine. Moving on to the definition of closed and open systems. A closed system is a group of objects that do not have a net force on them from any object outside of that system. They can still put net forces on each other. In a closed system, momentum is conserved. The total momentum remains the same. An example of a closed system could be this cart 1, cart 2 system. So we can imagine that these carts could move toward each other and impact each other, but when they do that, the only net force that they're experiencing, the only unbalanced force, is coming from the other cart, from something else inside of the system. It's not coming from anything outside of the system. So because these two carts are only putting forces on each other and not experiencing any net force from outside, we can see that the total momentum between them is going to be constant, because whatever change in momentum one cart receives, the other cart is going to lose. So in a closed system, the total momentum is constant, and this is an example of a closed system because there's no outside net force on these objects. An open system is a group of objects with a non-zero net force acting on them from some object outside of the system. In an open system, the total momentum changes, and the total momentum after is equal to the total momentum before, plus the impulse given by the outside object. So I'll give you an example of that. Let's say that I have just the cart system here. I'm just considering my system to be this one cart, and I reach my hand over to the cart and I give the cart a push. So I'm delivering some new impulse into the system from something outside of it. So this is now an example of an open system because there's some object outside of the system of objects putting a net force on the object. So the total momentum after here is going to equal the momentum that the cart starts with plus the additional momentum that the hand adds. That seems pretty simple. Whatever object is putting a force on the system applies that much impulse to the system, so the total momentum of the system changes by that much. And any open system could be a closed system if we just include all of the objects that are acting on each other. But the issue here is that if I start to do that, if I include the person in the system, this is now the cart person system, I also need to include the earth because the person is putting a force of friction on the ground to prevent themselves from moving, and the force of friction is being experienced by the earth. So the only way to have a system of objects in this situation that aren't receiving any outside forces is to include the person and the earth, not just the person. So you can turn an open system into a closed system, but in that situation the math actually becomes harder because the total momentum is staying the same here, but this includes the total momentum that the earth has, which blows up all our calculations and makes it impossible to calculate anything. So turning an open system into a closed system here is useless, and we want to keep some systems open so that we can do math more easily. This is a summary of what I said, and this is a general problem-solving tool for when to use the closed system idea and when to use the open system idea. If it's easy to find the momentum of each object, putting a net force on the other objects, put all of the objects in a closed system and find the total momentum. And if it's not easy to find the total momentum of each object, putting a net force on other objects, just put the easy to find objects in an open system and add the impulse from the outside object to the total momentum of the system. So in that open system example, we're keeping the hand and the earth outside of the system. Just as a quick note of another time you'll want to use an open system, it's basically impossible to calculate the momentum of particles of air. So if air resistance is adding to an unbalanced force on an object, you should call it an open system and leave the air particles outside of the system. Okay, I'll show you a quick example of using an open system and using a closed system. I'll start off with the sphere-sphere system where these two things are moving towards each other and only putting a force on each other. I can calculate the total momentum before using my momentum equations and remembering that one direction has to be negative. I'll call left negative here. When I do that, I find that the total momentum of this situation is 4 Newton seconds. So I can imagine that these two things hit each other and bounce away. The 5 kilogram object is now moving 1 meter per second to the left, and I want to know the velocity of the 3 kilogram sphere.
So using the idea that this is a closed system, so the total momentum remains the same, I can just say that that final momentum, the 5 kilograms times -1 plus the 3 kilograms times its new velocity, is equal to 4 Newton seconds. When I plug that in, I get a final velocity of positive 3 meters per second, so that means that after the 3 kilogram sphere is moving 3 meters per second to the right. So that's an example of a closed system because the spheres are only putting forces on each other and not experiencing anything from anywhere else. I'm now going to tilt this part of the surface down 30 degrees and imagine that the 3 kilogram sphere begins to roll down. And when it's rolling down, it's going to feel an unbalanced force of gravity from the Earth. So this is going to be an example of an open system. We can imagine that we want to know the momentum of the ball after 2 seconds of traveling down the hill. So I'm going to say that this is a sphere system, and it's an open system because there's going to be a force of gravity acting on it. So the total momentum after will be equal to the total momentum before, plus the impulse added by that unbalanced force. And I can see that the momentum before is just going to be the 3 kilograms times the 3 meters per second, plus the impulse of the force. And I know that impulse is equal to the net force times the time. I'm going to use a ramp problem setup to find the total force acting on this object. And when I do that, I find that this component of the force of gravity cancels out the normal force. So the total force on the object is the force of gravity times sine 30. Plugging that in using what I know about the ball gets me 14.7 newtons. So that's the net force on the ball. And I know that it's falling for 2 seconds. So therefore the impulse on the ball is 29.4 newton seconds. So the total momentum after here is 38.4 newton seconds. So that's what it means to have an open and closed system. This is going to come up a lot in future units, not just here. This is kind of laying the groundwork for understanding systems as a concept in physics. This last lecture in the momentum series is going to be about using momentum to predict what will happen in different types of collisions. There are 3 types of collisions when 2 objects interact. The first type is an elastic collision. This is what happens when 2 objects collide and do not attach to each other. They just bounce off of each other like this. One way I like to remember that is thinking about elastic things as being bouncy, like elastic bands and things like that. So in a similar way, an elastic collision is when 2 objects bounce off of each other. An inelastic collision is the opposite of an elastic collision. This is when 2 objects collide and attach to each other. So after the collision, they behave as one single object. And an explosion is when one object splits off into 2 objects like this. The big idea used in collision problems is that the total momentum in the whole system of the 2 objects is the same before and after the collision. We're going to be talking a lot about conservation in terms of collisions, not only in this unit, but also in the energy unit. And there's more to say about these types of collisions with energy, but for now, this video is only going to focus on momentum. So we use the conservation of momentum to predict the results of all 3 types of collisions. I'm going to start with 2 examples from elastic collisions. I'm going to say that right is positive and left is negative here, and the first problem says a 5 kilogram ball rolls to the right at 10 meters per second and collides with a 3 kilogram ball moving to the left at 6 meters per second. After the collision, the 5 kilogram ball rolls to the left at 2 meters per second. What is the velocity of the 3 kilogram ball after the collision? The first step to solving any collision problem is finding the total momentum in the system, because that's going to remain the same before and after the collision. So the idea of the total momentum staying the same is how we use information about what's happening before the collision to help us predict what's happening after. So we can see that before the collision, I have a momentum of 5 times 10 plus a momentum of 3 times -6. And that's going to be equal to the total momentum after the collision. And after the collision, the blue 5 kilogram ball is now moving to the left, so its velocity of 2 meters per second is negative, so its momentum is 5 times -2. And the momentum of the 3 kilogram ball is going to be 3 times the velocity that we're trying to solve for. So if you get a setup like this where you're able to set the momentum before the collision equal to the momentum after the collision and plug in all your variables, you usually only have one variable left to solve for. And if you only have one variable, you can always solve for that using algebra. Solving for v here using algebra, I find that v is equal to 14 meters per second to the right. So that means that after this collision, the 3 kilogram ball is going to move away to the right at 14 meters per second. Example number 2 says that a truck moving forward at 10 meters per second hits a 1,000 kilogram car moving forward at 5 meters per second. After the collision, the car moves forward at 11 meters per second and the truck moves forward at 6 meters per second. What is the mass of the truck?
So we can also use conservation to figure out information about the mass of an object. This example is an example of a collision that happens when both objects are moving in the same direction. So this can also happen. Objects can definitely still hit each other even if they're moving in the same direction, as long as the object behind the other one is moving faster than the object in front. So this is what the collision looks like. And we're trying to figure out the mass of that truck using the information that we have. And again, we know that the total momentum is remaining the same before and after the collision. So before the collision, the momentum is the momentum of the truck, which is m, its mass, which we're trying to solve for, times 10, plus the momentum of the car, which is 1,000 kilograms times 5 meters per second. And both velocities are positive here because they're both moving in the same positive direction. After the collision, the truck is moving at 6 meters per second, so that's what I multiply its mass by, and the car is now moving at 11 meters per second. And I know that these two equations are equal to each other because the total sum of the momentums before the collision is equal to the total after. Solving for mass using the setup gets me a final mass of 1,500 kilograms, so that's the mass of the truck. So that's pretty interesting. If we know the final velocities and initial velocities of two objects that are in a collision, we can predict the mass of one of the objects. There's a special rule for elastic collisions about hitting a wall. If an object hits a wall with an elastic collision, it bounces off with a velocity of the same magnitude and opposite direction that had originally pointed directly into the wall. As an example, if this 4-kilogram object moving at 5 meters per second hits the wall like this, it's reflected back with a new velocity of 5 meters per second in the opposite direction, like this. So I actually can't explain why this is happening right now. I'm going to explain why this happens in the energy unit. Notice that the total momentum of the ball does change here because this is now an open system. The wall is connected to the Earth. That's one reason why the momentum is changing. The other reason why the momentum is changing is because the velocity now points in the opposite direction. So if we call right positive, this ball started with a momentum of positive 20 newton seconds and ended with a velocity of negative 20 newton seconds. So the total change in momentum was actually negative 40 because you were going from positive 20 to negative 20. If an object hits a wall at an angle, the only part of the velocity that's flipped is the component perpendicular to the wall. So if you have an object moving toward the wall like this, the component of its velocity that's perpendicular to the wall is the blue arrow, the vertical arrow. So I'm going to flip that to the opposite side and same magnitude. The red arrow, the horizontal velocity, is parallel to the wall. So anything that's parallel to the wall is not flipped. So that's staying the same direction and the same size. I can see that the total velocity is now going to look like this, and the ball is going to move away from the wall like that. This kind of fits our experience of how objects hit walls. Notice that this means that the angle an object impacts a wall will always be equal to the angle it leaves the wall, because the two triangles are the same, they have the same magnitude, just with a different arrangement of where one of the components is. Okay, that was information about elastic collisions. We're now going to move to inelastic collisions. We're going to start with example number 1, a 70-kilogram football player moving right at 10 meters per second collides with a 60-kilogram player moving 8 meters to the left. After they collide, they move together across the field. What is their velocity? So the collision looks like this. So they're behaving as if they're one object. They're not actually, but because they're moving together, we can model them as if they are one single object. So I can see that the total momentum before the collision is going to be the 70-kilogram football player's momentum, which is 70 times 10, plus the 60-kilogram player's momentum, which is 60 kilograms times negative 8 meters per second. And I know that that is equal to the final momentum. But now the final momentum is going to look a little bit different because they're behaving as one big object. So if they're one big object, the mass of that one big object is actually just going to be the two masses of the objects before the collision added together. If a 70-kilogram player and a 60-kilogram player collide, they behave like a single 130-kilogram object. So using my equation for momentum, after the collision, I only have one object with one single momentum with a mass of 70 plus 60 and a velocity v that I'm trying to find. So I write that as m times v, which here is 70 plus 60, all multiplied by v. Using algebra to solve for v, I get that the velocity by itself is equal to positive 1.7 meters per second. So that doesn't only tell me the magnitude, it also tells me the direction that the two football players are moving after the collision. They're moving in the same direction that I defined to be positive, which was the original direction of the 70 kilogram player, which fits our intuition. If a larger object with a larger velocity hits a smaller object with a smaller velocity, we would expect that if they stick together, that single object will be moving in the same direction as the larger object rather than the smaller object. Let's do an example where both objects are moving in the same direction. A cart moves forward at 6 meters per second and connects with a 2 kilogram cart moving forward at 4 meters per second. After they connect, they move forward together at 5.33 meters per second. What is the mass of the first cart? So this is what that collision looks like. And this is the equation. Before the collision, the two momentums look like this. And after the collision, there's just a single momentum, the total mass times the total velocity. And I'm considering the mass of the first cart to just be a variable here that I'm trying to solve for. Solving for mass here gets me a final answer of 4 kilograms. If you plug that into the original equation, that comes out to be correct. So for inelastic collisions, you're always going to want to consider the two objects after the collision as one single object with a mass equal to the sum of the two smaller masses that made it up. I can now give you two examples of explosions. Let's say that we have a 50 kilogram astronaut floating in space, and she wants to get back to her space station. She has a 5 kilogram hammer that she throws at 20 meters per second in the opposite direction. How fast does she drift toward the space station as a result? So this is what that looks like. So I can see that the total momentum before anything happens is actually equal to 0, because both the astronaut and the hammer are not moving relative to the space station, before this collision happens. And after the explosion happens, when the one big object of the astronaut plus hammer splits into two smaller objects, this is what the total momentum looks like. We have the mass of the astronaut, 50 kilograms, times her velocity, which is what we're trying to solve for, plus the mass of the hammer, 5 kilograms, times its velocity, which is negative 20. It's very important that that's negative if we're considering the other velocity to be positive, because the hammer is moving in the opposite direction of the astronaut. Plugging this in, I can see that 100 newton seconds is equal to 50 kilograms times the velocity of the astronaut. So that means that if the astronaut throws that hammer away at 20 meters per second, she's going to drift at 2 meters per second back to the space station. You may have seen science fiction movies that use this trick, this idea that if an astronaut wants to get somewhere different and they're stuck, they can throw an object in the opposite direction of where they want to go, and they'll drift in the direction that they want to go. The reason why that happens is based on the conservation of momentum. If you have 0 momentum to start off, and then you throw something that's attached to you in one direction, you're going to move in the other direction to keep the total momentum equal to 0. Here's example number 2. A skateboarder at rest holds a 5 kilogram brick and throws it to the left at 5 meters per second. And if the skateboarder rolls away at 0.5 meters per second, what is their mass? I can see that, again, this is a situation where the starting momentum is 0, and the final momentum is equal to the brick's mass times velocity plus the skater's mass times the velocity. Solving for m gets me a mass of 50 kilograms, so that's the mass of the skater. We can talk about more complex situations where we have two-dimensional collisions. This is when collisions occur at an angle, and when this happens, we can use the fact that the total momentum on each axis stays the same to find missing information. Here's an example for an elastic collision. We have a 5 kilogram object moving to the right at 10 meters per second, and it collides with a 3 kilogram object and moves down at 8 meters per second at a 30-degree angle after the collision. So we can use this information to try to find the final velocity of the other ball, the 3 kilogram ball, after the collision. So let's start by finding the momentum in each direction, in each axis, before the collision and after the collision. So in the x direction, before the collision, I can see that the 5 kilogram ball has this momentum, 5 times 10, and the 3 kilogram ball doesn't have any momentum because it's not moving. And in the x direction after the collision, the 5 kilogram ball has this new x velocity using a trig to find that x component of the velocity. So its new momentum is going to be its mass times that new velocity. And the new x direction momentum of the 3 kilogram ball after the collision is going to be its mass, 3 kilograms, times its new x velocity, the velocity that it has only in the x direction. So I'm going to move this down here. And I can see that if the total momentum just in the x direction is conserved, then this equation is true, and I'm only missing one variable, so I can solve for that one variable, Vx. And when I plug that into my calculator, I find that Vx is equal to 5.12 meters per second in the x direction. So we know that that is 100% the case as long as this is an elastic collision. Now let's look at the y direction. I can see that in the y direction before the collision, there's nothing happening. Nothing is moving up or down at all, and so the y direction momentum to start off is just going to be 0 Newton seconds. After the collision, both objects are moving in the y direction. So I can see that the 5 kilogram object is moving at 4 meters per second in the y direction using trig, 8 times sine of 30. And I'm going to consider down to be negative here. So if I do that, I'm going to say that the momentum of the 5 kilogram ball is 5 times negative 4 meters per second. Looking at the y momentum of the 3 kilogram ball, I know that this has some velocity in the y direction. So its momentum in the y direction is going to be 3 kilograms times its velocity in the y direction. So I'm going to bring that down here. And again, I only have one missing variable, so I can use that to solve the problem. So solving that, I can see that the velocity in the y direction is 6.67 meters per second. And I can now use this information to find the total velocity using the Pythagorean theorem. When I do that, I find that the total velocity of the 3 kilogram ball is 8.41 meters per second. And this is at an angle of 52 degrees. I can find that using an inverse trig function. Because I have all three sides, I can use any inverse trig function that I want to find that, but the angle is 52 degrees on this ball. So that's an example of using conservation of momentum to predict the final movement of objects that hit each other at an angle. We can also do an inelastic example. These I actually think are normally easier than elastic collisions in 2 dimensions. We can imagine that this 5 kilogram ball is moving to the right at 2 meters per second, and the 3 kilogram ball is moving down at 2 meters per second, and they collide, stick together, and move off with some new velocity, and we want to know what that velocity is. So again, setting up this equation, in the x direction, I can see that the 5 kilogram ball has an x direction velocity of 2 meters per second, so its momentum is 5 times 2. And there's nothing happening in the x direction for the 3 kilogram ball. It's just moving up and down, so it has no Newton seconds of momentum. So that means that this is going to be equal to the total momentum of the single object after in the x direction. So that object has a total mass of 5 plus 3 kilograms, and a total velocity in the x direction, Vx. So I'll save that to solve in just a minute while I solve for the y direction momentum first. In the y direction, I can see that the 5 kilogram ball doesn't have any motion in the y direction before the collision, but the 3 kilogram ball does. The 3 kilogram ball is moving down at 2 meters per second, so its momentum is going to be 3 times 2. After the collision, again, this is a single object with a mass of 5 plus 3, and it now has a y direction velocity Vy. So this is the momentum that is happening in the y direction after the collision. So I can use algebra to find that the x velocity of this object is 1.25, and the y velocity is 0.75. And using the Pythagorean theorem, the total velocity is 1.46 meters per second. And using inverse trig functions, the angle is 31 degrees. So that's it. Those are a bunch of examples of solving problems with different types of collisions, elastic, inelastic, and explosions. All of these examples were just using the same fact that momentum is conserved along an axis as long as there are no outside forces on the objects. And the only difference is whether the objects behave as a single object or as multiple objects before and after a collision.
This lecture is going to be about uniform circular motion, which is what it sounds like, an object moving in a circle. Let's say that you want to make an object move in a circle. What would you need to do to it to make that happen? Well, you can't just let it continue with what it's doing without applying some force to it, because if you do that, it's just going to continue with whatever velocity it already had, according to Newton's first law. So let's say that you have this cart moving toward you with some velocity and you want to make it move around you. And I'm going to imagine that you have this rope that you extend out to the cart. To make the cart move in a circle as it goes by you, you'd have to apply a constant net force toward the center of the circle. That would cause the cart to move in a circle. So this is based on Newton's first law. An object maintains its velocity unless acted on by a force. So if that force from you disappears at any point, the object is just going to continue off with whatever velocity it had in the moment that you let go, in whatever direction that it had in the moment that you let go. And let's say that the object had no initial velocity. If it didn't have any initial velocity to start off, and you applied this force to it, it would just be dragged toward you without any circular motion. It's just moving toward you. So this shows that there are two requirements for circular motion. The first requirement is that the net force has to be constant and always pointing toward the center of the circular path. And the second requirement is that there has to be a constant velocity at a 90-degree angle to the net force itself. So this picture on the left kind of shows you what I mean by that. So both of these things have to be true for circular motion to occur. This gives us some vocabulary that we can use to talk about circular motion. The centripetal force is a name that we give to the net force on the object that's moving in a circle. It always points toward the center of motion, and it's measured in newtons. The tangential velocity is the distance the object moves around the circle over the change in time. It's measured in meters per second. The radius of the circle is just the radius of the circular path, which is measured in meters. And the centripetal acceleration means the acceleration that points toward the center. Because acceleration always points in the same direction as the net force, that means that in circular motion, the acceleration is always going to be pointing toward the center of the circle. So this picture shows you what I mean and how these variables are related over time. So you can see that as the circle goes around, the velocity is always pointing tangent to the circular path, parallel to the circular path, and the net force and acceleration are always pointing toward the center of the path. A common misconception about centripetal force is students often think that centripetal force is a type of force, like there's centripetal force and there's the force of gravity, there's the normal force, but that's not correct. Centripetal force is just the net total force that always points toward the center of motion, and any force can add together to make it. So as an example, when Earth is orbiting around the sun, gravity is the centripetal force. So the centripetal force is just a name that we give to whatever force happens to be pointing toward the center constantly. There's no such thing as a type of force called centripetal force. That's always made up of other types of forces. So some students are also confused about why the acceleration always points toward the center of the circle, whereas the velocity is always pointing tangent to the circle. One way to think about this is that the net force points toward the center and acceleration always points in the same direction as the net force. A second way is to watch the vector animation that's happening above my head. You can see that because acceleration is the change in velocity, it's causing velocity to always change toward the center of the circle. So the velocity continues to turn around, and that's why circular motion is maintained. If acceleration pointed in the same direction as velocity, the object would just continue along that straight line path. Another common misconception about centripetal acceleration is that it means that the object is getting faster and faster around the circle, but that's also not true. The role of the centripetal acceleration is to change the direction of the velocity, but it doesn't change the magnitude of the velocity, just the direction. So the velocity is staying at a constant rate. It's not getting bigger or smaller. The acceleration is just changing its direction as it turns around the circle. Two more vocabulary words that you'll need to describe circular motion are period and frequency. Period is the amount of time an object takes to complete one full cycle. We use the word period to describe a lot of different things. For example, class periods are cycles that repeat over a given amount of time. And just like that, a period in physics is just the amount of time that any cycle in physics takes to repeat. Here, in circular motion specifically, it means how long the object takes to go around the circle once, and it's always measured in seconds, and the unit for it is capital T. Frequency is the amount of repetitions a cycle completes in 1 second. So here in circular motion, frequency means how many times the object goes around the circle in 1 second. Frequency is measured in hertz or Hz. Hz just means events per second. So period is how long it takes for an event to repeat once, and frequency is how many events repeat in 1 second. So there's an interesting relationship there where the period is always going to be equal to 1 over the frequency. This is always going to be true. I'm going to give you a visual that's going to help you understand why. Let's say that you're going around a circular path and it takes you 4 seconds to go around the path altogether. Because it takes you 4 seconds to repeat this cycle once, that's your period. The period is 4 seconds long because that's the time it takes to repeat. The frequency is the amount of repetitions completed in 1 second. And if you look at my visual, you can see that in just 1 second, 1/4 of the total circle has been covered. So that means that the circle is being covered at 1/4 rotations per second. So the frequency here is going to be 1/4. And you can see from this that no matter what fraction I choose, the period is always going to be equal to 1 over the frequency. So here the period is 4 and the frequency is 1/4, and that is always going to be true. So if you have the period of some circular motion, you also have the frequency. One more important vocab word is angular velocity. I'm going to compare that to tangential velocity with this animation. In this animation, you can see I have a car driving in circular motion, and next to the car's path, you can see I put a boy sitting on some playground equipment that also spins in a circle. So when I make these two things start to spin, you can see that they're both spinning around the circle, but the car is covering a lot more distance over the same amount of time. So that means that the car has a much larger velocity than the boy. If you look down at the car's speedometer and looked at how fast the boy was going, you would see that the car is going much faster than the boy. So that's tangential velocity. That's how fast it's actually moving in meters per second. So you can see that the velocity of the car is much greater than the velocity of the boy. But there's another part of circular motion that we can look at where these two things are actually equal to each other. So the angular velocity is just the change in angle around a circle over the change in time. It's measured in radians per second. So it's a measurement of how many radians around a circle you go per second. So even though the boy's circular path is much smaller than the car's circular path, if you watch how many degrees or radians they go around the circle in a given amount of time, you can see that it's actually the same. They're covering the same angle of their respective circles in the same amount of time. That's useful information, so we record that in physics as a separate variable. Angular velocity. That W symbol is actually in omega, so when you're drawing that, you just need to make sure the two sides curl in like that. So you can see here that the angular velocity of the car, how much of an angle it covers over time, is actually equal to the angular velocity of the boy, even though the velocity, the actual tangential velocity of the car is much greater than the velocity of the boy. The car is much faster, but it goes around the circle at the same rate as the boy goes around his circle. So the angular velocity is the same, but the tangential velocity is different. So that was it for definitions for the first part of this unit. I'm going to show you the equations for this unit and where we get them. I'm going to start with an equation for the tangential velocity around the circle. We know that in general, velocity is displacement over time. Here, the object is going all the way around the circle once, and if the circle has a radius r, we know that the total distance that this object covered is equal to 2 pi r. That's the circumference of the circle. And based on our previous definition, we know that the time that it takes to complete one full circle is equal to the period of motion. The period is the amount of time in seconds that the object takes to rotate around the full circle. So our first equation that we're going to be using a lot is that the tangential velocity of any object is equal to 2 pi r over the period of motion, like that. And because period is 1 over frequency, we can rewrite that equation as tangential velocity is equal to 2 pi r times the frequency. So that's the first equation we're going to use. The second equation is for angular velocity. We know that angular velocity is the change in degree over time, or radians per second. And I know that if this object goes all the way around the circle, it covers 2 pi radians in that time. And the time that it takes to do that is the period. So that's going to be 2 pi over t is the angular velocity. And because t is 1 over f, I can rewrite that as 2 pi f. So that's an equation for angular velocity. And I'm going to keep this period and frequency equation up here as well. The next thing you might notice is that the tangential velocity is actually equal to the angular velocity multiplied by the radius. Each equation for the tangential velocity is actually equal to each equation for the angular velocity multiplied by the radius. So this equation is going to hold true. This is an equation for the centripetal acceleration of the object, how much it's accelerating toward the center of its circular path. I'm not going to prove that in this video, it's a little complicated, but if you're interested in knowing where it comes from, I've left a proof in the description of the video. So centripetal acceleration, acceleration toward the center of motion, is equal to the tangential velocity squared over r. And the centripetal force on an object is the net force. So just like in regular straight line physics, the net force is equal to m times a, here the centripetal force is equal to mass times the centripetal acceleration, which is also equal to mass times v squared over r. So in conclusion, this is all the new vocabulary for the unit. There's a lot, but once you get used to using it, each individual idea is pretty straightforward. I'm going to end the video with 2 examples of circular motion problems and what they look like. A 1,000-kilogram car takes 4 seconds to turn from north to west around a corner. If the radius of curvature of the road is 30 meters, what force of friction do the car's wheels apply? So we can imagine this car going around the circle, and the force that's taking the place of the centripetal force here is going to be the force of friction. This is because it has to be some force pointing toward the center of the car's circular path, so that has to be some horizontal force. And the only horizontal force that can exist here is some push from the road itself, which kind of makes sense because if the road is slippery, if there's ice,
it's much more difficult to turn. Your car just keeps going with whatever velocity it already has. So the force that's acting as the centripetal force here is the force of friction. So we know that that is what we're trying to solve for. This says that the radius of curvature of the road is 30 meters, which means that if this curve continued to curve into a complete circle, that circle would have a radius of 30. So that's going to be important for our calculations. The mass of the car is 1,000 kilograms. And because it takes 4 seconds to turn from north to west, I know that that's going to be 1/4. That turn is 1/4 of the total circle that you're seeing. So if that takes 4 seconds to turn, altogether the total circle would take 16 seconds for the car to turn around. So the period of motion here is going to be 16 seconds. So I have the radius, the mass, the period, and I need to find the centripetal force. So looking at my centripetal force equation, I'm probably going to need to solve for what Vt is, because I can plug in my mass and I can plug in my radius. And I know that Vt by itself is equal to 2 pi r over capital T, so plugging that stuff in, I get 11.8 meters per second. Plugging that into the original equation, I get that the centripetal force on the car is 4,641 newtons. A lot of the unit is going to be like this, where you're picking out individual pieces of information and plugging it into equations. There are some parts that are very conceptual, but a lot of it is just learning to recognize which variable is what and plugging in the information correctly. Here's example 2. The distance from the Earth to the Sun is 149.6 million kilometers. How fast is the Earth moving around its orbit? What is the Earth's acceleration toward the Sun? So this is an example of a problem that gives us some context clues for solving it. We're trying to find the tangential velocity and the centripetal acceleration of the Earth. And we're given the radius of Earth's circular path. Because if the distance from the Earth to the Sun is that far, and the Sun is in the center of the Earth's orbit, that's also going to be the radius of the Earth's orbit. This is going to come up a lot. So if I convert that number to scientific notation and convert it to meters, I get 1.496 times 10 to the 11th meters for the radius of that circular path. So to solve for the tangential velocity, I need the radius and the period. And the problem doesn't give me the period. But I actually know that using the context of the problem, because the period is how long in seconds the object takes to go around the circular path once. And I know that it takes the Earth 1 year to complete its circular path. That's what a year is. So a year is 365 days, so I just need to convert that to seconds. And when I do that, I get that the period is 3.15 times 10 to the 7th seconds. Plugging that into 2 pi r over t, I get 2.98 times 10 to the 5th meters per second. And the centripetal acceleration is just v squared over r, so just plugging in my numbers here, I get this very small acceleration for Earth. It makes sense that it's accelerating at such a small rate because it's only changing its direction at a very small rate, because it takes a full year to completely change its velocity's direction all the way around the circle. So that's how you solve circular motion problems. A lot of it is just going to be drawing out those variables, plugging them into the equations, and finding missing information. Problems where you have to find centripetal force or use centripetal force can be very challenging. But I think that if I give you 5 examples of different situations where you have to find it, you'll be able to use these examples in solving problems, because most of the centripetal force problems that we do in physics fall into one of these categories. I'm just going to go through these 5 examples one at a time and explain what's going on in each, why the forces that are present are what they are, and how they're related to each other mathematically. Before we begin, I want to look at an interesting pattern that shows up in horizontal circles and in vertical circles. If the circular path of your object is perfectly horizontal, that means that the net centripetal force is also perfectly horizontal. So this means that all y components cancel out. So whenever you're dealing with a circle that's happening in the horizontal direction, you know that all the forces in the y direction are going to cancel, and all the forces in the x direction are going to constantly add together to equal the centripetal force, which is equal to mv squared over r. So you can use that math to find what the sum of the forces will have to be. And if the circular path of an object is perfectly vertical, the net force or centripetal force can be vertical or horizontal, but it always has to exist on the plane of the circle itself. So a circle is two-dimensional, and the force always has to exist on that plane. It can never point outside of it. Those 2 facts are going to be really important for problem solving and in helping us thinking about these situations. The first 3 situations are going to be about horizontal uniform circular motion. We're going to start with something simple. Let's say that you have an object resting on a horizontally spinning surface, and we want to understand what the centripetal force on the object is. I'm going to start by drawing a free body diagram of this person standing on this spinning surface. I know that the force of gravity is always present, and because this is a surface and the person is not accelerating in the up or down direction, the normal force must perfectly balance out the force of gravity. Because they're spinning horizontally, there must be some constant horizontal force pulling them toward the center. In this case, the only place where that horizontal force can be coming from is from friction, because the only thing that can apply that horizontal force to the person is the surface. So if the surface is applying a force that's parallel to the surface itself, that must be the force of friction. So we know that the force of friction is always pointing in toward the center of the circle, which kind of makes sense. If you're standing on a spinning surface, your feet have to physically stick to it to continue to spin. If it's slippery, you're just going to fly off the spinning surface. So making a force table for the centripetal force, and again, the centripetal force is just the net force on this person, it's not a type of force. The centripetal force in the x direction must equal mv squared over r because it's a horizontal circle, and in the y direction it must equal 0 because it's, again, a horizontal circle. All the vertical stuff must cancel out. So that's how we know that the force of gravity and the normal cancel out, and the only thing happening in the x direction is the force of friction. So I can see here that the force of friction is going to be equal to the mass times the velocity squared over r. So if the problem were asking for any of those, I could use properties of the frictional force to calculate those additional values. Let's say now that I give this person something to hold on to as they spin around. So they're holding on to this bar as they spin around the circle. If they're holding on to this bar, that bar is helping them stay in the circle, and that would be the applied force that they're applying there because they're holding on to the bar. So because they're applying that force on the bar is applying the same force back on them, so I would call that the applied force. So we can see now that there are two forces pointing toward the center of the circle. There's the force of friction and the applied force, and they're both adding together to make mv squared over r. So this is what the free body diagram would look like. But m and v squared and r didn't necessarily change in this problem. I'm going to imagine that the circle spins at the same rate that it did before. So if those didn't change, then the sum of these two forces has to be equal to what it was before, that same mv squared over r. So that would mean that these two forces connected tip to tail have to be equal to that original sum of the forces, which means that the force of friction is going to have to be much smaller here than it was before to make those two things add together correctly. So this kind of makes sense. If you're holding onto a bar as you're spinning in a circle, the applied force is kind of helping out the force of friction, and your feet have to do less work pushing back against the surface to keep you moving in a circle. So if you hold on, it's easier to continue to move in a circle because your feet require less friction. So if you have a bar and you don't just have the force of friction, then you have both the force of friction and the applied force pointing toward the center, so the sum of those two will equal to mv squared over r. And you can get additional information out of the problem that way that you can then use to solve for missing forces. For example, if you had a way of calculating the centripetal force and you had a way of knowing what the applied force was, you could use those two to calculate the force of friction. So now let's go on to the next example. Again, I'm going to unpack the forces that are present here and how they're related to each other mathematically. I had already expressed in a previous video that when a car is turning, the force that's making it turn, the centripetal force, is the force of friction, because that's the force that the road pushes horizontally against the car with. And if there were no force of friction, if the road were icy, as an example, the car would just skid off in whatever direction it was going and it wouldn't be able to turn. So the force of friction here is acting as the centripetal force and is equal to mv squared over r. Making a free body diagram of this car, I have a force of gravity going down, a normal force going up, and a force of friction constantly pointing toward the center of the circle, like this. So when I make my force table, this is what shows up. The normal force is pointing up, the force of gravity is pointing down, and it's not accelerating up or down because its net force points toward the center of the circle, which is horizontal here. So the force in the x direction is just equal to the force of friction, and that's mv squared over r. So that's how you would understand the relationship between the forces on a turning car. I'm going to change the situation a little bit here now. This is a really common problem in IB physics specifically. I'm going to now imagine that the road that the car is on is banked, which means that it's angled in a way to help the car make the turn. So the car is now sitting on an angle as it goes around the circle. This is a very common trick designers use to make it easier for things to turn. For example, NASCAR tracks are banked in this way where they're at an angle so the cars can more easily turn around them. And a lot of school running tracks are also banked, and runners find that when they're on that bank, it's much easier to make the turn than if the track were perfectly flat. So why is this? What force situation is causing it to be easier for this car to turn when it's on this bank? Making a free body diagram of the situation, I can see that I'm going to have a force of gravity down, that's always the case, an upward normal force, and I know here that the net force has to point straight toward the center of the circle because this car is trying to turn perfectly horizontal. It's not trying to get higher or lower on this banked road at all, it's just trying to turn in a circle. So its net force has to point toward the center because it's the centripetal force, so the net force has to be perfectly horizontal. The only force here with a component pointing in the direction of the net force is the normal force. If I break that up into its x component and its y component, this is what it looks like. If you do the math, you'll find that the angle of the ramp is actually equal to that top angle of the normal force. So this is equal to the normal force times cosine of the angle, and this is equal to the normal force times sine. I'm going to take these now to my table so I can understand how they're related to each other. In the vertical direction, I can see that I have the normal force times cosine pointing up, and the force of gravity pointing down, and those two things are adding together to make 0. And I know that they're adding together to make 0 because if this is a horizontal turn that the car is making, there's no total vertical force because the net centripetal force also has to be horizontal. So the normal force times the cosine minus the force of gravity has to equal 0, so those two things are actually equal to each other. In the x direction, I can see that the only thing that's happening is the normal force times the sine of the angle. So this normal force must be the centripetal force on the object. If you write this out, you get that the centripetal force is equal to the normal times sine of the angle is equal to mv squared over r. So that's some interesting information that we can get out of banked road. On a banked road with no extra friction helping the car out, the normal force times sine is equal to the centripetal force, and the normal force times cosine and the force of gravity cancel each other out. This is notably different from a ramp problem that we've been doing in the past. There are a few different reasons for this. The main one is that in a banked circular motion problem, the centripetal force has to point perfectly horizontally because that's the direction that the object is turning. But in a ramp problem, the centripetal force normally points down or up the ramp, so it's at an angle. So if the net force is pointing down or up the ramp, that's normally the situation where we tilt the axis to make it easier. But here the net force is not pointing up or down the ramp, it's pointing perfectly horizontally to keep the object moving in a circle, and so the relationship between the forces change. This means that in a banked circular motion problem, the purely vertical forces cancel each other out, whereas in a ramp problem, you still have some vertical and horizontal component of your net force if you don't tilt the axis. Another notable difference is that in a ramp problem, the force of gravity is greater than the normal force because the normal force is equal to one smaller component of the force of gravity, whereas in a banked circular motion problem, the normal force is greater than the force of gravity because the force of gravity is now equal to just one component of the normal force. Moving on to example 3, this will be the last example for objects spinning in the horizontal direction. This is an example of tension at an angle. We're going to imagine that we have a ball attached to the end of a wire, and the wire is angled in a certain way, and it's spinning around in this horizontal circle like this. So you're normally given some angle like this, and you're asked to find information about the ball based on its motion. One thing you'll notice is that if this is the length of the rope, the radius of the ball's path is actually going to be equal to the length of the rope times the sine of the angle of the rope, because that's the opposite side of the right triangle that's formed when I draw that radius. So if you need to find the radius of motion for your equations, that's how you would find it, the length of the rope times the sine of the angle. This is a free body diagram for the forces that are on the object. It's just the force of tension, and the force of tension always points in the direction of the rope or wire that's creating it. And then there's the force of gravity, which always points straight down. And there's no other force on this object, so these are the only two forces that are present. To understand why this object is moving in circular motion, we can break up the force of tension into its y component and its x component like this. I'm also going to move the angle over here because that's a similar angle to the vertical, and I can use that to find missing information about my x component and y component. So I can see that my y component here will be the force of tension times cosine, and the x component will be the force of tension times sine. So to understand the relationships between these, I just plug these back into my table. So I know that in the x direction, the net force will equal the centripetal force, mv squared over r, and in the y direction, because it's not turning in the y direction at all, the net force will equal 0. There are two things happening in the vertical direction here. There's the force of tension times cosine up, and the force of gravity down, so those two things must add together to make 0. And in the x direction, the only thing that's happening is the force of tension times sine of the angle. So that is going to be equal to mv squared over r here. So again, I can use this equation to find missing variables, and I can also use this equation to find missing variables. It really depends what information you're given, but this information you can draw out of that circular motion situation, given the table and your understanding of what will add together to make the net force. Okay, 2 problems left. Part 2 is on vertical uniform circular motion. So these are examples of objects that are moving in circles in the vertical direction. A really common example is a hill and a trough. You can see here that I have a car going over a hill, and this is actually an example of circular motion if we consider the hill to be part of a massive circle. Obviously, the car is not actually going to go around this full circle, but as long as it's on a part of the circle and it has a constant velocity, it is technically in circular motion. The radius of this full imaginary circle is called the radius of curvature. So if a problem tells you that a hill has a radius of curvature of so many meters, what it means is if this hill were extended into a full circle like this, this would be the radius of that full circle. Let's look at the forces that are present on the car. The only two that need to be present are the force of gravity down and the normal force up. And I'm going to assume that the normal force is smaller than the force of gravity. And the reason why I'm assuming that is that I know that the net force always has to point toward the center of the circle. And here, the center of the circle is straight down from the car. It's at the very top of that possible circle. So the net force has to be pointing down, so the force going down has to be bigger than the force going up. When I add these two forces together like this using vector addition, I get the net force. I get the centripetal force on the car. So this means that when an object is at the top of a circular hill as it's going over with a certain velocity, its net centripetal force is going to be equal to the force of gravity minus the normal force, and it's also going to be equal to mv squared over r. A lot of problems might ask, what is the maximum speed that the car can go over a hill and still be in circular motion? So what that means is that if I increase the speed of this car, you'll notice that because the centripetal force is equal to mv squared over r, the centripetal force will increase when the speed increases. And the more the centripetal force increases, the less normal force you're going to need to add together to make that. And it can continue to increase like this until it hits the force of gravity. There isn't any other force pushing down that can affect the car, and the force of gravity can't get any bigger because it's just determined by the car's mass and the acceleration of gravity on Earth. So because the force of gravity can't get any bigger, this is the maximum net force down that you can have on the car, and so this means that this velocity, where the net force is just equal to the force of gravity, is where the car is moving at its fastest velocity. The car achieves its fastest speed if there's no normal force at the top of the hill. So if the centripetal force is just equal to the force of gravity, that's where the maximum speed of the car occurs. So that's kind of physics code. If there's no normal force, that means that the velocity is at its highest, and if the velocity is at its highest, there's no normal force at the top of the hill. Now let's imagine that the car is in a trough that's at the bottom of an area like this. Here I know that the normal force is going to be bigger than the force of gravity because the net total force has to point toward the center of the circle. And here, the car is at the bottom of its circular path. So the force going up has to be bigger than the force going down, and I can't change the value of gravity, but I can change the normal force. So the normal force has to be bigger than the force of gravity. And when I add these using vector addition, I can see that this will be equal to the centripetal force. So in a trough at the bottom of a car's circular motion, the centripetal force is equal to the normal force minus the force of gravity, and those are also equal to mv squared over r. So you can use those equations to find additional information. Okay, this is probably the most complex example, example number 5. If you can master this one, you're basically going to be good for the rest of the unit in terms of circular motion. So objects can go at constant velocity around a loop-de-loop like this, and as they go around, we're going to need to understand what forces are acting on them to make that net centripetal force. So I'm going to have this car go around a few times and just fill in what information I know about the car. I know first of all that because it's moving at a constant velocity around the loop-de-loop, the net centripetal force has to be the same value at all locations and always has to be pointing toward the center of the loop. So if I make this go around and I choose 3 points to look at these 3 points, this is what the centripetal force looks like. At the bottom, it's going to be pointing straight up. On the side, it's going to be pointing to the left. And at the very top, it's going to be pointing straight down because it always points toward the center of the object's motion. Now let's have it go around again and see what the force of gravity is doing at each point. I know that gravity always points straight down and doesn't change based on the location of the car. So these are what the forces of gravity look like at each point along the car's motion. Okay, now that I have the force of gravity down and I know what the net force has to be, I need to decide what can I add to the force of gravity to make the net force point in that upward direction. And here at the bottom, the only thing that can be pointing straight up is the normal force. So that means that the vector sum of the normal force pointing up minus the force of gravity going down is going to be equal to the net force pointing up. So using vector addition, I'm going to start at the tip of the force of gravity and draw that normal force all the way up to the top of the centripetal force, and I know that the red and blue vector add together to make the purple vector. So the normal force has to be bigger than the force of gravity on the bottom in order to make this work, in order to make the centripetal force point in that upward direction. Because that purple vector is the vector sum of the two other vectors working against each other to create that single purple vector. Looking at the second point, I need to decide what forces are present here. First of all, the only force that can be pointing toward the center here is actually the normal force again, because the normal force always applies at a 90-degree angle to the surface that's creating it. Here, it would apply outward from the surface because the surface is pointing up and down, so the normal force can point left or right. Here it's pointing left, straight into the circle.
And because there's no other force present to push the car into the center of the circle, the normal force here has to be equal to the net force. And because the normal force is equal to the net force, that means that there can't be any vertical forces here. So if there's no net vertical force, there has to be some force in the upward direction preventing the car from slipping down as a result of gravity. So that force is actually going to be friction holding the car up, allowing it to continue its motion. So the force of friction here is balancing out the force of gravity going down. Okay, going up to the top, I can see here that the force of gravity is not yet big enough to match the centripetal force. I drew the centripetal force a little bit bigger, so that means we're going to need an additional push down, and the only thing that can provide that is, again, the normal force, because the normal force always applies at a 90-degree angle to the surface that's creating it. So here, it's pointing straight down toward the center of the circle. Connecting those tip to tail, those two vectors add together to make the net force there. So that's what a force diagram would look like at each point along the loop-to-loop. So at the bottom, I can see that the centripetal force is the normal force minus the force of gravity. On the side, I can see that the centripetal force is equal to the normal force, and gravity is equal to the force of friction. And at the top, the centripetal force is equal to the value of the normal force plus the value of the gravity. There, they're pointing in the same direction, so they're working together to create that centripetal force. Okay, I'm now going to ask, what is the smallest velocity that this car can go around the loop-to-loop with and still make it all the way around in circular motion? So I need to figure out what is the smallest value that the centripetal force can be as a result of the velocity. So I've put that equation above my head. You can watch what happens. As the velocity begins to shrink, the centripetal force begins to shrink as well, because the velocity is in the numerator, so less velocity will mean less centripetal force. Watch what happens to each of my force diagrams as the centripetal force shrinks. Because we can't change the value of gravity, we have to change other forces to make the sum of the forces equal to the centripetal force. So I'm going to play this animation a few times. Watch what happens as the centripetal force gets smaller. So the minimum that the centripetal force can be is the force of gravity, because at that top point, if the centripetal force got any lower, that would mean that the force of gravity somehow got lower than it actually is. And we can't change the force of gravity because that's only dependent on the object's mass and the acceleration of gravity. So we can't make that net force any smaller than it actually is. So that means that if the velocity got any smaller than where it's at now, the car would just fall off toward the top of the loop-to-loop, because the actual force on it, the force of gravity, would be greater than the centripetal force that it would need to maintain its circular motion. So the minimum velocity that the car can go is determined by when the centripetal force is equal to the force of gravity at the top of its motion. So when a problem asks what is the minimum speed an object can go around a loop, it really means what velocity will make the net force equal to the force of gravity. That's physics code for that situation. At the bottom, you'll also notice some other interesting patterns. You can see that because the centripetal force is equal to the force of gravity at the top, it also has to be equal to the force of gravity at the bottom, but because they're pointing in opposite directions, the normal force actually has to be 2 times the force of gravity to create that centripetal force. So the centripetal force will be equal to 0.5 times the normal force. At the bottom, it'll be exactly half as big as the normal force. On the side, the same situation will hold. The force of gravity will be equal to the normal force at that point, because the normal force is equal to the centripetal force, and we can see at the top the centripetal force is equal to the force of gravity. So because normal is equal to centripetal, and centripetal is equal to gravity, normal is equal to gravity. And on the top, the centripetal force is just equal to the force of gravity, and the normal force is equal to 0. And again, this is only true when the velocity of the car is at its minimum possible velocity to create that centripetal force. That was a lot. If you didn't completely understand that, it's okay. You're going to have a lot of practice with this and a lot of chances to experiment with it. I would suggest coming back to this video as you go through the problem set, as you're having trouble, and referring back to some of the examples. Once you master these basic examples, every other circular motion problem is going to be some iteration of these basic situations. This video is going to be about the idea of work in physics. Work has a very specific definition and equation that we're going to go into. Work is basically a force applied on an object multiplied by the distance or displacement that the force is applied for. The specific definition is that it's an object's displacement multiplied by the component of force parallel to the displacement. The variable for work is W, and the unit is J, which stands for a joule. And the equation for work is equal to the force times the displacement s times the cosine of the angle between them. I'll explain why that equation looks the way it does using this picture. Let's say that you want to push this box along this displacement s, and to do that you apply this force in this upward and rightward direction here. We can imagine maybe this is a rope or something dragging the box along. And there's a certain angle between the force and the displacement that you're moving the box. So the displacement and movement look something like this. So our definition says that work is equal to the component of the force that's parallel to the displacement multiplied by the displacement. And not all of that force is parallel to the displacement. So that force has two components, an x component and a y component that look like this. And you can see when I draw those out that only one of those components is parallel to the displacement, which is the force times the cosine. That's the x component in this case. So you can see that the force times the cosine of the angle is equal to the force component that's adjacent to the displacement, which, according to our definition, is the component that we need to calculate the work. So the work here is going to be equal to the component that's adjacent to the displacement times the displacement, so that's where we get the equation force times the displacement times the cosine of the angle between them. Some patterns show up here. You'll notice, for example, that if a force is perfectly parallel with the displacement, the angle between them is equal to 0, and cosine of 0 is just 1. So that means that the force times the displacement times the cosine is just equal to the force times the displacement, which makes sense because the whole force is parallel, so we don't really have to worry about angles or components at all. If the force is perfectly perpendicular to the displacement, we know that the cosine of 90 degrees is 0, so that actually means that the whole work equation is going to 0. So if you have a force applying at a perfectly perpendicular direction to the displacement of the object, that actually means that the force is not doing any work on the object, as we understand work in physics. Work can be positive or negative, but the rules for when it's positive and negative are different from when vectors are positive and negative. And in fact, work is a scalar. It has a magnitude, but it does not have a direction. I'm going to give you a reason why. Let's say that I define right as being positive and left as being negative. In this case, I have a force pointing to the right and a displacement pointing to the right, so I can see that the force is positive and the displacement is positive, so that means that the work is also positive. If I flip these around and I consider the rightward direction to be negative now, I now have a negative force because right is negative, and a negative displacement because right is negative, but when I multiply those two things together, I still get a positive work. So whether work is positive or negative has nothing to do with the specific direction that the force and displacement are pointing. Whether they're pointing positive or negative by themselves doesn't affect the sign of the work, so work does not depend on a particular direction. We can see that work is always positive if the parallel component of the force points in the same direction as the displacement. So what work actually depends on, and whether work is considered to be positive or negative, is whether the force and displacement point in the same direction as each other or in the opposite direction as each other. So as an example, if the force points in the negative direction and the displacement points in the positive direction, I can see that the work is going to be negative here. And if I switch these around, now the force points positive and the displacement points negative, but the work altogether is still negative. So what's determining whether the work is positive or negative is not the direction of just the force or just the displacement. It's how those two things relate to each other. So we can't say that work by itself has a direction in the real world, because it's based on other things that have directions, but it itself does not. So work is always negative if the parallel component of the force points in the opposite direction of the displacement. We can talk about the work done on the object by specific forces, or the total work done on the object. So we use language for both. There are two ways to find the total work done on an object. We can either add the work done by every force on the object. If we add all the individual works of all the individual forces, we get an overall total work done on the object. Or we can just use the net force on the object as F in our work equation. If we just add up all the forces to find the net force, that's another way of finding the total work done. I'll give you an example of what I mean. Let's say that we want to find the work done by every individual force on this object, and then find the total work done. So I'm just going to go through one at a time and look at the work done by each force as this box is moved 5 meters to the right. Starting with this 10 Newton force, I can see that because this is perfectly perpendicular to the displacement, you'll remember that that means that the total work done is 0, because the angle is 90 degrees and cosine of 90 degrees is 0. The work done by the 8 Newton force is going to be the force times the displacement times the angle between them, and here the angle is just 0, so that means that cosine is just 1. So the force times the displacement is 8 times 5, which is 40, and that's measured in joules, J. And again, this downward force here of 10 is perpendicular to the displacement, so that means that it's going to have a total work of 0. And this 3 Newton force is pointing in the opposite direction of the displacement. And you'll remember from the previous slide that if the force is pointing in the opposite direction of the displacement, the work is always considered to be negative. So this is going to be negative 3 times 5, which is equal to negative 15 joules. So the total work done on this object over those 5 meters I can see is 25 joules. If I add up the work done by each individual force, it adds together to make 25. And like I said, the other way you can calculate the total work is by finding the net force on the object. And I can see here that the net force, if I cancel out the 10 going up, the 10 going down, and the 3 takes away from the 8, I get a total net force of 5 going to the right. So here the net force is 5, and the displacement is 5. There's no angle between the net force and the displacement. So the total work is equal to 25. So those are 2 different ways of finding the total work done on the object. Here's an example of calculating work. A person pulls a 10 kilogram box 10 meters along a horizontal floor with a rope that applies 100 newtons, angled up at 30 degrees. If the coefficient of kinetic friction between the floor and box is 0.5, what work is done by the rope, by gravity, and in total on the box? It's always helpful to start these by drawing a free body diagram, so that's what I'm going to do. This says that there's a force going up and to the right of 100 newtons at an angle of 30 degrees. So if I break this into its x component and y component, this is what it looks like. There's also a force of gravity going straight down, which I can find just by multiplying the mass times gravity. So I know that this object is not moving up or down at all, so that means that the total force in the y direction has to add together to make 0. So I can see that I have an upward force of tension of 50 as one component of my force of tension. So if I put that on my force table above my head and add that to the force of gravity going down, which I'll consider negative, I know that in total, these forces have to add together to make 0. So that means that the normal force to add to those things to make 0 has to be equal to positive 48 newtons. So that's going up. To figure out the force of kinetic friction, I can just say that the force of kinetic friction is equal to the coefficient times the normal force. That's my equation for the force of friction. Multiplying the coefficient by the normal force gets me 24 newtons, so that force is going to the left, because it always opposes the motion of the object. Now that I have this complete free body diagram, I'm just going to enter in information about the x component of the net force above my head, so I can see that I have a force of tension of 86.6 newtons, and a force of friction of negative 24 newtons, so altogether the net force is 62.4 newtons to the right. So the work done by the rope is going to be equal to its force times cosine times the displacement. And I already know the force of tension times cosine of 30 degrees is just 86.6 newtons, and that's pointing in the same direction as the displacement, so I'm going to consider that to be positive work. So I multiply that force times the displacement of 10 to get 866 joules. So that's the work done by the rope. I can see that gravity is pointing at a 90-degree angle to the displacement, so because it's at a 90-degree angle, the cosine of that is just 0, so the total work done by gravity is 0. And to find the total work done on the box, I can just use my net force in the work equation, and I know that the net force is just pointing in the horizontal direction. I can see above my head that it does not have a vertical component. So because it's just pointing in the horizontal direction, in the same direction as the displacement, the angle between it and the displacement is 0. So that means that the cosine is 1, so I just have to multiply the net force by the displacement, and when I do that, I get 624 joules of work done in total on the box. The reason why this is lower than the work done by the rope is that the force of friction is taking away, it's adding negative work to the box. So if I add the negative work from friction to the positive work from the rope, I get a total work done on the box of 624 joules. Here's another example. A person carries a 10 kilogram bag of groceries up a 6 meter high flight of stairs to their apartment. How much work did they do on the bag? So this is what it looks like. They're moving up at a constant velocity up the stairs. I'm going to start by making a free body diagram for this bag. I know automatically that there's a force of gravity of 98 newtons going down, and if this bag is moving up the stairs at a constant velocity, that actually means that the forces only need to balance out. There doesn't need to be any kind of special force pointing diagonally up the stairs, because if it's moving at a constant velocity, we just know that the net force has to make zero. So if the person applies an upward force that's equal to the downward force of gravity applied on the bag, that will be enough to keep it moving at a constant velocity. So if the bag pulls down with 98 newtons, the person pulls up with 98 newtons. So that upward force is what we want to focus on as they move up, because we're asking how much work does the person do on the bag, not how much work is done in total on the bag. I can see that this force applied by the person is parallel to the vertical displacement and perpendicular to their horizontal displacement as they go up the stairs. So that actually means that the horizontal displacement isn't going to come into my equation at all, because the work done over the horizontal displacement by this force is just zero because it's perpendicular to the horizontal displacement. So it's only the vertical displacement that matters when calculating the work done by this person. So here the work is 98 times 6, which is equal to 588 joules. So for this person to move the bag up the flight of stairs, they had to do 588 joules of work on the bag. I'll do one more quick example. We can imagine we have the same situation, but now we're given the full length of the stairs of 10 meters and the angle of the stairs. So they go up stairs that are angled at 30 degrees, and they walk for 10 meters up those stairs. And they're applying the same force to the same bag. So in this situation, we just have to solve for what their horizontal and vertical displacements are. When I do that using trig, I find that they went 5 meters up, and it doesn't actually matter how far they went to the right, because that rightward component is perpendicular to the force, so it's not contributing to the work done at all. Because they're going up 5 meters and the force that they're applying is 98 newtons, this is going to be 98 times 5, which is equal to 490 joules. So that's the basics of how you use the equation for work and the concept of work to solve for the work done. In the rest of this unit, we're going to explain why we care about work so much. It's actually one of the big foundational problem-solving tools in physics, and that doesn't entirely become clear until we talk about energy in the next lecture. This video is going to be about the definition of work, the definition of energy, and how they connect. The definition of energy is that it's a measurement of the amount of work an object can do, the total amount of work that an object can do. There are different forms of energy because there are different reasons why an object can do work, apply a force across a displacement. However, all the forms of energy are still energy. They're all different ways of measuring the same thing, the ability to do work. Energy is a scalar, like work. It has a size but no direction. The variable for energy is capital E, and the unit of energy, like work, is capital J for joule. To illustrate what I mean by energy, I'm going to imagine that we have a blue box that we're going to do some work on, and another object that has energy inside of it that can do work on the blue box. I'm going to imagine, for example, that this orange box has 40 joules of energy inside of it. I'm going to pretend that we don't know exactly where these 40 joules of energy are coming from. You just have to know that this thing has 40 joules of energy. So the reason I'm doing this is to show you what it means to have those 40 joules of energy. Basically, for that orange box to have 40 joules of energy means that it can do exactly 40 joules of work on the blue box. It can't do more than that based on its situation, but it can do 40 joules of work. So as an example, if this orange box can apply a force of 1 Newton on the blue box, that means that it could apply that force of 1 Newton for 40 meters, because 40 times 1 is equal to 40 joules, and that's the equation for work. So it could move like this if the orange box is applying 1 Newton on the blue box. If the orange box is applying 2 newtons on the blue box, that means it could push it for 20 meters, because again, the work is the force times the displacement, so that's 2 newtons times 20 meters, which is equal to 40 joules. So both of these things are possibilities. We don't know exactly which one will happen when the orange box hits the blue box. That depends on other factors in our situation, but all of these are possible because the orange box contains 40 joules. If the orange box put 4 newtons on the blue box, that means it could push it 10 meters, because 4 times 10 is equal to 40. So again, it would be doing 40 joules of work. So I think you can see the pattern here. This actually also gives us a new definition of work. Because energy is a measurement of how much work an object can do, the object loses energy when it does work. So as an example, we can imagine that this orange box is applying 10 newtons on the blue box,
and it has 30 joules of energy inside of it. You can see that so far, before anything has started to move, the total work done is 0. It hasn't moved any displacement yet. But if the orange box moves the blue box forward by 1 meter, it's done 10 joules of work. So that means that if it could do 30 joules before and then it did 10, it can now only do 20 joules of work. And then if we move it another meter, we can see that this blue box has been pushed forward 2 meters by 10 newtons of force, so the total work done is 20. And if at the beginning the orange box could put 30 joules of work on an object and it's put 20, now it only has 10 left. So at the very end right here, the total work done is 30 joules, so that means that there's no energy left in the orange box. It's done all of the work that it can do on the blue box. So you'll notice that the work done is equal to the change in energy of the orange box. By the time 20 joules of work have been done by the orange box's energy has changed by negative 20 joules. So work is equal to the change in energy of an object. Here's an example of using that equation. A box has 80 joules of energy, and if we use a rope at a 60-degree angle that applies a 100 Newton force to drag it 10 meters across the floor, how much energy does it have after this event? So if we drag it that far, I can see that the component of the force adjacent to the displacement is going to be 50 because it's cosine of 60 degrees, which is 1/2 times the force, which is 50, times 10 meters. So the work done is 500 joules. So that means that if this box starts with 500 joules, then the final energy is going to be its initial energy plus the change. So it went from 80, added 500, and so the total is 580 joules. That's how much energy it ends with. So the work done on an object, the parallel force times the displacement, is equal to the change in energy of the object. You'll notice an interesting pattern here. Because of Newton's third law, if one object does positive work on another, the other object does the same amount of negative work on the first. So because of Newton's third law, if the orange box is putting 10 newtons to the right on the blue is putting 10 newtons to the left on the orange. So if they're moving to the right, the orange box is supplying positive work to the blue, and the blue is supplying the exact same amount of negative work to the orange. So because work is change in energy, this means that whenever one object loses energy, the other object gains the exact same amount of energy. So if you observe the picture that I've made, after 1 meter, the orange box has lost 10 joules of energy because it did 10 joules of work, and the blue box gained 10 joules of energy because it had 10 joules of work done on it. And then after 2 meters, the orange box is down to 10, and the blue box is up to 20, and then finally the orange box has 0, and the blue box has 30. So you'll notice that the total energy is remaining the same. So because of Newton's third law, and because whenever one object gains that much energy, the other object must lose the exact same amount of energy, energy cannot be created or destroyed. So it's another conserved quantity. So the law of conservation of energy says that energy can never be created or destroyed, only transferred from one object to another or transformed from one type of energy to another type of energy. So this is a little bit different than momentum. In momentum, there aren't different types of momentum, it's just m times v. But with energy, there are a lot of different types of energy. There are different reasons why an object can apply a force over a time. But even though there are different types, the total amount of energy in a situation, as long as it's a closed system, remains constant. It remains the same, and the total amount of energy in the universe has never gone up or down. Just as a reminder, a quantity that is conserved can never be created or destroyed, only transferred or transformed. And these are the quantities that are conserved in physics. So far we've gone through momentum and energy, and we've also touched on mass not being created or destroyed. So like I said, there are different types of energy because there are different reasons why an object has the ability to do work. However, all types of energy measure the same quantity, how much work an object can do. In the next few lectures, we'll talk about these specific types of energy in detail. This video is going to be about kinetic energy, one of the types of energy. Kinetic energy is the energy that an object has as a result of moving. If an object is moving, it can impact another object and push it a certain displacement with a certain force until it comes to a stop. Thus, because an object is moving, just that fact gives the object the ability to apply a force over a displacement, which is the ability to do work, which is energy. So as an example, if this truck is moving with a certain velocity, when it impacts this box, it can apply a certain amount of force for a certain amount of displacement. We don't know exactly what force or what displacement right now, but we know that it has that ability to apply some force for some displacement, so it must have some energy because it is moving.
So the energy that an object has because it is moving is kinetic energy. The variable for kinetic energy is E subscript K, and the unit is J, or joule. All energy is measured in joules. Based on this definition, if kinetic energy is based on an object's mass and velocity, how quickly it's moving, there must be an equation for the object's kinetic energy that only uses mass and velocity. So far, we've only talked about energy in terms of work, force times distance, or displacement. But here, because this object is moving, because it has a certain mass and a certain velocity, there must exist some equation that can tell us exactly how much work it can do, just as a function of its mass and its velocity. So we're going to try to figure out what that is. So using this truck's mass and velocity, how can we figure out how much force it can apply for how much displacement? So I know that this object's kinetic energy is equal to the total force it can apply times the total displacement it can travel until its velocity is equal to 0, because once it's stopped, it can no longer continue to apply that force. By Newton's third law, I know that whatever force it applies to the object also applies to it in the reverse direction, which seems like it's going to matter because that's affecting the truck's motion, so that's probably going to help us understand how much force it will take to make the truck come to a stop. So I know that if the truck pushes the box forward with this much force for this much displacement, the truck itself is also pushed backwards by the same force for that same amount of displacement. And here, I'm assuming that that force backwards is the only force acting on the truck, basically because these two objects are the only two things exchanging energy. I'm imagining that the force of gravity and the normal force are balancing each other out. So this force backwards on the truck is equal to m times a, the mass of the truck times the acceleration of the truck. So this is Newton's second law that's telling me that the net force on the truck is equal to m times a. So I'm going to go back down into my equation and rewrite that kinetic energy formula as the total force times the total displacement the truck can apply in terms of this new equation for the force that I have. So because that force on the truck is pointing in the opposite direction of the displacement, I'm going to consider the acceleration that it creates to be negative if the displacement is positive. So I'm going to call that m times negative a times s. I'm going to refer back to one of the kinematics equations, v squared equals u squared plus 2as, because I now have information about s and a, and I also know information about the final velocity of the truck. The final velocity of the truck here is 0, so I can rewrite this equation like this. If I rearrange the equation like this, I want to know information about the starting velocity of the truck and the mass. My ultimate goal is to get an equation for kinetic energy that just uses mass and the starting velocity of the truck, because those should be the only two things that are giving it energy if kinetic energy is really just based on how fast a certain object is moving, is the initial velocity and the mass. So solving this for initial velocity gets me that the initial velocity is equal to negative 2 times a times the displacement. So that means that negative a times s is equal to 1/2 u squared. So I can actually take negative as in my equation for kinetic energy and replace it with 1/2 times the initial velocity squared, like this. And when I do that, I actually get the equation for kinetic energy as it's used in physics. So the kinetic energy that an object has, the total amount of work it can apply on another object as a result of moving, is equal to 1/2 times its mass times its velocity squared. That's normally written as v rather than u because it's not normally considered to be an initial or final velocity, it's just the velocity that an object is moving with. So the equation is 1/2 times m times v squared, because as you saw in the proof, that's the exact amount of work, the force times the displacement, that the object can apply as a result of its mass and velocity. I'll do a few examples here just to show you how to use the kinetic energy equation. A 1,000 kilogram truck moves at 20 meters per second. What is the truck's kinetic energy? So I can see that I'm given the mass and the velocity. The mass is 1,000 and the velocity is 20 meters per second, and the equation is 1/2 mv squared. So just plugging these in, I get 1/2 times 1,000 times 20 squared, which when I multiply that out is equal to 200,000 joules. Students are often a little thrown off by the numbers involved in energy. They'll get numbers this big and assume that it's too much. Just for context, 1 joule is about the amount of energy that it takes to lift 1 apple by about 1 foot. So if you think about it, if you have a 1,000 kilogram truck going at 20 meters per second and it impacted like a gigantic pile of apples, it could probably move a lot of them a lot, basically. So 1 joule is really not very much energy, if that's a helpful way of thinking about it. So 200,000 joules definitely makes sense for this problem. Here's another example problem that combines work and kinetic energy. A 1,000 kilogram truck moves at 10 meters per second when it collides with a large box. After it pushes the box 5 meters, the truck is moving at 5 meters per second. What is the average force the truck puts on the box? So I have the mass of the truck, the initial velocity of the truck, and the final velocity of the truck, and the displacement that the truck pushes the box. So using this information, I can find that the kinetic energy that the truck starts with is 50,000 joules, plugging in those numbers. And the final kinetic energy with the final velocity is 12,500 joules. So that means that the change in energy is negative 37,500 joules. And if you remember, the change in energy is equal to the work done by the truck. In this case, it's the truck doing the work, it's giving its energy to this other object. So that means that it's doing 37,500 joules of work on this other object. So I know that this other object is experiencing that much work, and that's equal to the force it experiences times the displacement, and the displacement of the object is 5 meters. So that means that the average force that the object experiences as the truck is slowed down is 7,500 newtons. So that's a connection between kinetic energy and work. Just one important note, energy is a scalar, and kinetic energy is also a scalar, which means it can never be negative. It has size but no direction, so just observe how this is different from momentum. If I calculate the momentum of these two objects, one is positive and one is negative, but when I calculate the kinetic energies, they're both positive. This actually makes sense because if we're considering one velocity to be positive and the other velocity to be negative, the squared velocity in the kinetic energy equation actually gets rid of that negative sign. So the kinetic energy is always going to be positive regardless of what direction the object is moving. So that's one way it's different from momentum. So here you'll notice that the total momentum is 11 newton seconds and the total kinetic energy is 53.5 joules. So the momentums are working against each other, but the kinetic energies are adding together. One last thing to note, because kinetic energy and momentum both only depend on mass and velocity, we can actually write an equation for one in terms of the other. So this is actually given to you on your IB test booklet. The kinetic energy is equal to the momentum squared over 2 times the mass. It's pretty easy to prove this if you're given the equation for momentum, mass times velocity. This is going to be very important when we start to talk about collisions involving both kinetic energy and momentum later on in the unit. So that's it. That's the definition of kinetic energy and the equation for kinetic energy. This video is about gravitational potential energy, which is another type of energy. Gravitational potential energy is the energy an object has as a result of its ability to fall. As long as it has a vertical displacement or height that it can move down, it can push or pull objects with its weight until it hits the bottom of that height. The variable for gravitational potential energy is EP, and the unit again is J for joule. All energy is measured in joules. So I'm going to show you why objects have this energy. Let's say that I have this orange box M attached to a rope that's attached to a pulley which is attached to another object. Let's say that this object is on a frictionless surface. So if the surface that the other object is on is frictionless, that means that just because this orange box has the ability to fall and to be pulled down with gravity, this orange box can actually pull the other object a certain displacement with a certain amount of force. So just because it has the ability to fall and because it has a mass, it has energy. It has the ability to apply a force on that purple box for a displacement. Gravitational potential energy is the easiest type of energy to figure out the equation for, because if this orange box is pulling down with the force equal to its mass times gravity, because that's the gravitational force on it, we can assume that the purple box is experiencing that same amount of force from the small box, just m times g, and the displacement that the purple box is moved over is exactly equal to the height that the orange box falls down. So if this orange box has a certain height that it can fall from, that means that it can displace another object by that exact amount of height and use its own force of gravity as the force on the other object. So because the work done is equal to the force times the displacement, here the work done by the orange box is going to be the force of gravity times the displacement. And I can see that the displacement that the purple box travels is exactly equal to the height of the orange box. So that means that the displacement is equal to the height, and I know that the equation for gravity is m times g. So that means that the total work that an object can do as a result of its height and mass is equal to m times g, the acceleration of gravity, times h. And that's the equation for the gravitational potential energy, m times g times h. So this is pretty simple to use. I'll give you a few examples. A 2-kilogram ball sits on top of a roof 4 meters above the ground. How much gravitational potential energy does it have? So pretty simple. We're given the mass. We're given g is always 9.81 on Earth, and the height is 4 meters. So the potential is m times g times h, so I multiply 2 kilograms times 9.81 meters per second squared times 4 meters, and that's equal to 78.5 joules. So this has exactly 78.5 joules of potential energy. Here's another example. It's a little more complicated. A 5-kilogram ball sits on top of a track that consists of a 10-meter long ramp at an angle of 30 degrees and a 5-meter long ramp at an angle of 60 degrees. How much gravitational potential energy does it have at the top of both ramps, and how much gravitational potential does it have at the top of the lower ramp? So I'm going to figure out how high up in the air it is, because gravitational potential only depends on the vertical height. It does not depend on any kind of diagonal height that you have on a ramp. That's a really common misconception. It only depends on the vertical height. Using trig, I can see that the vertical height of that first ramp is 8.7 meters, and the height of the second ramp is 2.5 meters, just 10 times sine of 60 and 5 times sine of 60. So when I add these together, I see that the total height that the ball has at the top is 11.2 meters, and the mass is 5, g is 9.81 meters per second squared. So multiplying these out, I can see that the potential energy here is 549 joules. So if it rolls down here, it's now only at that lower height of 8.7, so the height is 8.7, mass is 5, g is 9.81, so the potential energy is m times g times h, which is 427 joules. So that's how you calculate the potential energy at different heights. One thing you may have noticed is that the position you choose for your base height of 0 is completely arbitrary. When we get to conservation of energy, you will be able to choose any height to be 0 and still solve the problem. For example, you may be watching this video and looking over at something on a desk, and that thing may have a certain amount of potential energy because it has a certain amount of height relative to the floor. But that height isn't necessarily the farthest it can fall, because you may be on the second floor of a building. So it could potentially fall all the way to the ground outside if we consider that to be the total distance it can fall. And we can imagine a really crazy scenario where that ball just keeps rolling and rolling after it falls until it gets to the Grand Canyon, and when it's there, it could fall even more. So the exact height that an object can fall is kind of arbitrary. It's set by humans. As long as you keep the 0 point of that height consistent throughout your whole problem, the math will work out and make useful predictions. So don't worry too much if it seems arbitrary. It is ultimately. Like, what we decide to be 0 is based on what works for our problem. One last thing to note. Often the phrase, the work done by gravity, is used as a code word for the object's starting gravitational potential energy. For example, if a 10-kilogram object falls 5 meters, the work done by gravity on the object equals the gravitational force times the displacement, which is equal to its potential energy, which there would be 490.5 joules. So that's what you have to know about gravitational potential energy. This video is going to be about elastic potential energy, another type of energy. But before we talk about elastic potential energy, we need to talk about a property of springs, because elastic potential energy is all about springs. I'm going to give you 2 new variables. The first variable is delta x. This means the displacement of a spring from its natural length. And the other variable is Fs. This is the force applied by a spring on an object. So this is the spring force. The spring force always points towards a spring's natural length position. So I'm going to show you what that means. Every single spring with an object attached to the end has some natural length where it naturally moves to if there's no force applying to the spring at all. It just naturally comes to rest at some central spot of the spring. You only experience a force from a spring if you stretch it or compress it away from its natural position. So right here, at its natural position, we would say that the stretch of the spring, the displacement of the spring, is equal to 0 meters. And here, because the spring isn't being stretched or compressed at all, the force that the spring is itself applying is also equal to 0 newtons. This vector shows you how far the spring has been compressed away from its starting position. So the length of that vector is delta x. It's the displacement of the spring away from its natural length. And the force that the spring applies on the object always points back towards the central position, which makes sense. If you try to push a spring in to compress it, the spring naturally pushes against you back towards where it was originally. So these two things always point in opposite directions. If you displace a spring in one direction, it pushes back on you in the other direction. And if you displace it more, it's going to push with more force back. If you stretch a spring out, it's still being displaced, just in the other direction, so that means that you're going to experience a force on the object pushing back toward the center in the opposite direction of the displacement, like this. The next piece of information I need you to know is lowercase k. This is called a spring constant. A spring constant is a measurement of the force that the spring applies per meter that it's stretched. The equation for the spring constant is k, the constant, is equal to the force that the spring applies over delta x, the stretch or compression of the spring. And the units of that are newtons per meter. So every spring has its own k constant. The smaller the spring constant of the spring, the weaker the spring is, the less able it is to apply force. So if you have a spring that has a k constant of 20, that means that for every 1 meter that you stretch or compress it, it applies 20 newtons of force. So if you compress it for 3 meters, it will apply 60 newtons of force. So that's what the k constant tells you. This is related to Hooke's law, which is going to be important for understanding this topic. Hooke's law says that the force from a spring is equal to the negative k constant times delta x. The reason why it's negative is only because the force always points in the opposite direction of the displacement. So if the displacement is positive, we need something to switch the sign to make the force negative, so we multiply it by a negative. And if delta x is negative, we just multiply it by a negative to make a positive force. So that's the only reason why the negative exists in Hooke's law. So Hooke's law says that if you displace a spring by this far, it's going to put exactly this much force, negative k times delta x, back in the other direction toward the center. Here's a quick example of using Hooke's law. A 5 centimeter spring with a spring constant of 200 Newton meters is stretched to 8 centimeters. What force does it apply? So if this is the natural stretch of the spring at 5, that's its natural real length, and it's stretched to 8, the actual stretch of the spring is 3 centimeters. So the displacement of the spring is 3 centimeters, which we usually convert to meters when we're working with force. That's 0.03 meters. And we know that the k constant is 200 newtons per meter. So that means that the force that the spring is going to apply at this point is equal to 200 newtons per meter times 0.03 meters, which is equal to 6 newtons. Okay, so you now have enough information to talk about elastic potential energy. Elastic potential energy is the energy stored in a spring that has been stretched or compressed from its natural length. When the spring is released, it will apply a force for a displacement until it returns to its natural length. So it has the potential to do work. It has the potential to apply a force for a displacement, so it has energy. The variable is a little confusing because the variable for elastic potential energy in your IB textbook is the same as the variable for gravitational potential energy. They're both EP. I might replace it throughout the course with EEP, elastic potential, or ESP, spring potential. All three of those work fine, but on the IB test itself, it's just going to be EP. The unit for elastic potential energy is also joules, because everything in energy is measured in joules. So just to visualize what happens when this spring is released, as it begins to be displaced, the spring is applying a force on it, but it's applying less and less force as the object gets closer and closer to the center. By the time it hits the center, there's no force left, and the spring stops applying force. So it can only do that much work. So if elastic potential energy is based on a spring's stretch and strength, there must be an equation for a spring's elastic potential energy that only uses the stretch and the spring constant k. But we have a problem here. We can't use work is equal to force times displacement to calculate the work done by the spring because the force is constantly changing here. The force isn't constant. The force is getting smaller and smaller until it gets back to the spring's natural rest point and then it hits 0. So we can't use work equals force times displacement because we don't have a single consistent force to plug into that equation. So the way that we're going to solve this is to make a force displacement graph to find the work done. So I'm going to explain why in just a moment. I'm just going to need you to follow along. This is probably the most complex proof in this unit. I'm just going to need you to follow along with the visual for a minute. So if the spring is stretched by this much, by delta x, that delta x is going to be the displacement that the object starts away from 0. That's how far it is away from 0 at the beginning. And the total force that the spring is applying at that exact point by Hooke's law
is equal to negative k times delta x. Here I'm going to consider that to just be positive just to make the graph a little simpler, and I'll consider that to be positive k times delta x. So I'm going to put a dot on my graph. I know that when the spring is displaced this much by delta x, the force experienced is k times delta x. I also know that when the spring is back at its 0 position, at its rest position, the total force supplied is also 0, because there's no displacement, so by Hooke's law there's no force either. So at 0 meters of displacement from the center, there's going to be no force on the spring, so I can put another dot there on my graph. So now I just need to decide what the middle part of this graph looks like. Is it going to be a straight line, or is it going to be a curve? Well, I know that the relationship between force and displacement looks like this. Force is equal to k times delta x. And you'll notice that that's modeling a linear equation, where force is on the y-axis, delta x is on the x-axis, and k is the slope, and there's no y-intercept. So if you graph the force from a spring over the displacement, it produces a linear line with a slope of k and y-intercept of 0 newton. So we already decided that the y-intercept makes sense as 0 because at 0 meters it's not supplying any force to the object. So this is going to be a straight linear line with a slope of k. So that's what the graph looks like. Okay, this is something we haven't gone over in detail yet, but the area under the curve of a force displacement graph is equal to the work done by the force. This makes sense because the y-axis is measuring force and the x-axis is measuring displacement. So if you're finding the area made up of one side of force and one side of displacement, you're multiplying those two things together in some way, and when you multiply force and displacement together, you get work as a result. So the area under the curve of this graph is equal to the work done by the spring. So if we can figure out what that total work it can do is as a result of its initial displacement delta x, then we'll have an equation for the elastic potential energy of the spring. So just to visualize it, this is what doing that work looks like over time. It starts with a lot of work, but as it gets closer to 0, it's applying less force over the same amount of displacement. So that means that it's doing less work as it gets closer and closer to 0. So because work is the area, and that area is the area of a triangle, which I know is equal to 1/2 base times height, I can see that the base of this triangle is equal to delta x, and the height is equal to k times delta x. So I'm going to plug those in to base times height, and when I multiply that out, I get 1/2 times k times delta x squared. And that is equal to the equation for elastic potential energy. So the total potential an object has as a result of being stretched on a spring is equal to 1/2 times the spring constant times the stretch of the spring squared. So using this equation, I'm going to solve a few problems. A spring of spring constant 50 newtons per meter is stretched 20 centimeters from its natural position. What is its total elastic potential energy? So I know the k constant is 50 newtons per meter and delta x is 20 centimeters. And you always want to convert centimeters into meters when you're doing this because you're dealing with other things like energy and force that are dependent on meters. So plugging this in, the elastic potential energy is 1/2 kx squared. So when I plug these numbers in, I get a total potential energy of 0.01 joules. Pretty small, it makes sense. This is a pretty small displacement with a pretty normal amount of spring constant. Here's another example. A spring of k equals 200 newtons per meter is already stretched by 3 meters from its natural position. How much work would be required to stretch it to 5 meters? So I know the k constant and the initial stretch and the final stretch, so I'm going to write those there. I'm now going to calculate the initial potential energy and the final potential energy of the spring. So the initial potential is 900 joules and the final is 2,500 joules if I plug those numbers in. So right away you'll notice that the stretch being squared is making the change in stretch matter quite a bit. Like 2,500 is much bigger than 900, even though the stretch didn't even double. So I know that the work done is equal to the change in energy. The work required to move this spring from 3 to 5 is equal to the change in energy that we give to the spring. So here, because it went from 900 joules to 2,500 joules, the change in energy is 1,600 joules. So that's equal to the work done on the spring. So that's how you deal with elastic potential energy. This video is about thermal energy or heat energy, another type of energy. Thermal energy is the energy associated with heat and temperature. Thermal energy appears as a result of friction, air resistance, impacts, and other interactions between objects.
Thermal energy is actually a measurement of the random kinetic energy of vibrating particles in an object. We're going to talk about this more in a future unit. For now, I just need you to know that what thermal energy is, what our experience of temperature and heat actually is really just the random vibrations of atoms and molecules in a substance. There's nothing else to it. The variable for thermal energy is a little strange. It's capital E subscript INT. This means internal energy. The reason it's called this is because this is the internal kinetic energy that an object has because of all the random movement of the particles inside of it, if that makes sense. So even if the object isn't moving, the particles internal to it might still be moving back and forth, and so it has some internal thermal energy. The unit for thermal energy is, again, J for joule, because all energy is measured in joules, and again, it's just the ability to do work. As a general rule, thermal energy is almost always calculated by finding how much energy has been lost from an object or system. Energy is never truly lost because it can't be created or destroyed, but if it's turned into thermal energy, that usually means that we can't use it again, just because thermal energy is more difficult to capture and use than other types of energy. Here are a few examples of transforming energy into thermal energy. Friction transforms kinetic energy into thermal energy, so if an object is moving along the ground and it encounters friction, it's going to have less kinetic energy than before. And what's happening there is that the amount of kinetic energy that it lost was transformed into heat energy. And that heat energy can stay in the object, it can go into the floor, it can go into the environment around it. Thermal energy has a tendency to spread out like that. I'm using thermal energy and heat energy interchangeably here. I should probably just stick to thermal energy. We can calculate the specific amount of thermal energy that's created using friction, because friction creates thermal energy. So as an example, if this frictional surface is 5 meters long and it applies a 10 Newton force of friction back on this object, I know that the work done by friction is equal to negative 50, 10 newtons times 5 meters, and the two things are pointing in opposite directions, so the work is negative. And so if the friction is doing negative work, what that means is that it's taking energy out of the object. It's taking exactly 50 joules out of the object. So that means that the exact amount of kinetic energy lost to thermal energy is exactly equal to the work done by friction, which is 50 joules. So if this object was moving with a certain amount of kinetic energy, it just lost 50 joules of that kinetic energy to thermal energy. We can also calculate the total thermal energy created if we know the kinetic energy before and after. Like if before we find that this object had 200 joules of kinetic energy, and after it only had 150 joules of kinetic energy, we know that the internal energy, the thermal energy created in that interaction is 50 because it lost 50 joules of energy. When an inelastic collision occurs, when two objects stick together, some kinetic energy is lost to thermal energy. Sometimes it's all of the kinetic energy. For example, when a ball falls on the ground and stops moving, all of its energy is transformed into thermal energy. Some of it may be lost to sound energy, like when you drop a ball, you normally hear it hit the ground. So some of its energy was transformed into sound, but most of the energy lost during a collision like that, where an object stops moving due to a larger object, most of that energy is actually going into heat energy. The only other place it can go is really sound energy, and sometimes light energy. When you have an inelastic collision and two objects stop moving, all or some of their kinetic energy is also transformed into thermal energy, and the energy stays in the objects and also moves into the air around them. Just as an example of using numbers for this first one, some problems might ask you how much heat energy is created when a ball falls to the ground. So if you're given the mass and height of the ball, like if the ball is 5 kilograms and it's 5 meters above the ground, you can calculate that the gravitational potential of the ball is 245 joules. And right before it hits the ground, all of that potential energy has been changed into 245 joules of kinetic energy. And then when it hits the ground, all of that energy is dissipated as heat energy. So it loses 245 joules of energy to heat to the environment around it. We're going to be talking about collisions a lot more later on in this unit, so I'm going to hold off on talking about specific equations for inelastic collisions right now. Just one thing I need you to know is that in a perfectly elastic collision, no kinetic energy is lost to thermal energy or sound energy. This is actually the technical definition of an elastic collision. A perfectly elastic collision is one where not only is the total momentum conserved, but the total kinetic energy also remains exactly the same and no energy is lost to heat or sound. So that's what you need to know about thermal energy. We're going to be working with this idea a lot in this unit and in the future. This is going to be a quick video on other types of energy that exist in physics. You're not going to need to know how to calculate these types of energy in this unit. You're just going to need to understand what properties of objects cause these types of energies to be present. The first type is electrical energy. Electrical energy is the energy carried by electrons. People normally use electricity to deliver energy created in power plants to buildings where we convert it into other types of energy that we use, like light energy, heat energy, kinetic energy, etc. But while it's moving to us through the wires, it exists as electrical energy. So basically, if you have a power plant that normally converts some type of heat or chemical energy into electric energy, which is then delivered to your home where you use it as light energy or heat energy or kinetic energy or other things to power your day. The unit of electric energy, as with all other types of energy, is the joule. I'm going to stop saying that because every single type of energy is measured that way. Some examples of electric energy. Electrical energy exists in circuits. Lightning could also say your nervous system, stuff like that. All of those things involve electrical energy. Sound energy is the energy carried by sound waves. In almost all collisions, at least some kinetic energy is transformed into sound. Sound itself is a wave of energy moving through a medium like air or water, etc. The energy moves through without carrying the matter along with it. In a very, very future unit, like next year future unit, we're going to spend a lot more time talking about the specific properties of sound, but for now you just need to know that it's a wave of energy. Chemical potential energy is the energy stored in the bonds between atoms or ions. It can be released or stored in chemical reactions. A common example of chemical energy is food. Actually, that comes up a lot in physics because the place where we get most of our energy to do things, our own ability to apply forces over distances and displacements, really all just comes from the food that we eat and the chemical bonds in that food that we are able to break up and use as energy and transform into the kinetic energy and potential energy and other things that we use throughout the day. Another example is gasoline. That's how we power our cars, is in the chemical potential energy of gasoline. That's how we're able to apply forces over displacements with our cars and other vehicles. Batteries also involve chemical potential energy. Radiant energy is the energy carried by light and other forms of electromagnetic radiation like X-rays, microwaves, radio waves, gamma rays. Again, we're going to be talking about a lot of this specifically next year. For now, you just need to know that light and radiant energy is a type of energy. So visible light, radio waves, Wi-Fi, cell signals, microwaves, these all fall into radiant energy. And the last type of energy is nuclear energy. This is the energy released during nuclear fission or fusion. It's contained within the nuclei of atoms until it is released. You don't need to know too much more about it than that right now. Examples of nuclear energy are nuclear power stations, obviously, nuclear bombs, and the sun. The sun is actually powered by nuclear energy as well. So those are the other types of energy that you need to know about. This lecture is going to be about open and closed systems in energy, which work a little bit differently than open and closed systems in momentum. You will remember from the momentum unit that a system is a group of objects, and we can choose objects to be in our system based on how the concept helps us solve problems. Because energy works differently than momentum, we're going to use systems in a slightly different way than we did with momentum. So basically, there's going to be a different rule for when something is an open and closed system, because there are different rules for when energy leaves a system as opposed to when momentum leaves a system. Before we go any further, we need to define mechanical energy and non-mechanical energy. Mechanical energy is any type of energy associated with the motion and position of an object that we can easily calculate and predict. So without even giving you the examples of mechanical energy here, I think that you could probably predict based on that definition that kinetic, gravitational potential, and elastic potential energy are the three types of mechanical energies. They're the only ones with very specific equations associated with them, and the types of energy associated with an object's motion and position. Non-mechanical energy is any type of energy that's not mechanical energy. All of these other types of energy do not depend on an object's position or movement, and they're a little bit harder to calculate and predict in general. Using this new definition, I can now say that a closed system in energy is a system where the only energy transfer and transformation that happens involves mechanical energy. And in a closed system, energy is not transferred to objects outside of the system. The total energy of the objects in the system stays the same. A very common example of a closed system in energy is something like a ball compressing a spring. So right now, because of the stretch of the spring, the ball has a certain amount of elastic potential energy. And it doesn't have any kinetic energy or potential energy. So the total energy of the ball is all elastic potential energy. All of that energy is stored in elastic potential, which is a type of mechanical energy.
So the idea of a closed system in energy is that if the only transformation of this energy that happens is from one type of mechanical energy to another type of mechanical energy, that means that the total amount of energy in the system will remain the same even if the specific type of mechanical energy changes. As an example, we could let this ball go, and as it begins to move, the potential energy is lost and kinetic energy takes its place. So the elastic potential energy is being converted into kinetic energy. So it can roll like that for a little while, and you'll notice that now all of its energy is kinetic energy, and that's the same amount of energy as it had when it was compressed into the spring. It's just that before, that mechanical energy existed in the spring, and now it exists in the object itself, but it's the same total energy. And then if it starts to go up a hill, it's going to rise to a certain height, and as it rises its height, it's going to lose kinetic energy and gain potential energy. But again, the idea is that if just a transformation of mechanical energy is happening, that means that the total energy in the system is going to remain the same. The energy is not actually leaving that ball, it's just being transformed from kinetic energy to potential energy. And when it gets to the top, all of its energy is potential because it's come to a stop, so it doesn't have any kinetic left. And because the total energy of the ball remains the same, even in reverse, we know that if we drop the ball from the same height that it rose to in the first situation, it will actually compress the spring to the exact same length that it compressed the spring in the other situation, because the total energy is remaining the same. So the total gravitational potential at the beginning will equal the total elastic potential at the end. Another example of a closed system is when mechanical energy is transferred from one object to another. For example, if we have a perfectly elastic collision between two identical spheres, you can see that one is just giving the other its kinetic energy, but the total amount of kinetic energy between them is remaining the same. This is actually true for all elastic collisions. An open system in energy is a system where energy is transformed from mechanical to non-mechanical energy, or vice versa, or mechanical energy is transferred from or to an object outside the system, and the total energy in the system changes. So just like in momentum, in an open system, the total momentum changes. Here in energy, in an open system, the total energy in the system changes, but the reasons for that are different. An example of an open system could be mechanical energy being lost to heat due to friction. Friction on the ground actually performs the function of transforming kinetic energy into heat energy. So as this box slides across the floor, the friction that it experiences generates heat energy, which is really coming from its kinetic energy. So after it slides, some of that energy is no longer in the box and can't be retrieved by the box. It's in the air and in the ground as heat because of friction. So that energy was lost from that system. It wasn't destroyed because energy cannot be created or destroyed. It just no longer exists in the box and it can't be easily retrieved. Now that the heat is in the air, it's just going to be lost to the atmosphere as a whole. Another example of an open energy system is whenever you hit the gas on your car. There, non-mechanical energy is transformed into mechanical energy. So this car starts with no kinetic energy and no mechanical energy in general, but as you hit the gas, it begins to get more and more kinetic energy. So that's an example of a change in the mechanical energy of a system, so we would say that that's an open system. And that energy still has to come from somewhere, it can't be created or destroyed. Here specifically, that energy is coming from the chemical energy in the gas in the car. So you can gain as much kinetic as you lose in chemical energy. So that's the basic idea of an open and closed system with energy. The big idea of this unit is that energy cannot be created or destroyed, which is going to help us solve problems with it. This lecture is about LOL diagrams, which are a very specific way that physicists represent how energy is changing in a system. LOL diagrams all look like this, which is why they're called LOL diagrams. You can see it looks kind of like LOL. Basically, there are two graphs of energy with a circle in the middle to describe the objects in a system. Specifically, the graph on the left means the amount of energy before an event happens. The graph on the right means the amounts of energy after an event. And the circle in the middle is where you draw objects in the system we're looking at. So when we're considering a system, we have to consider which objects are a part of our energy system. I'll take you through a bunch of examples and show you how to construct an LOL diagram for each one. For the first few examples, just keep in mind that in a closed energy system, the total energy has to be the same before and after. So when we're adding up the total amount of energy in these LOL diagrams, we're going to have to make it the same. So I'll give you a few examples of that. Let's say that we have a box compressing a spring that is not moving.
So because this box has no velocity and it has no height, but it's compressing a spring, the only type of energy that's present right now is elastic potential energy. In a lot of these problems, these specific numbers will not be given. LOL diagrams are commonly used to qualitatively describe energy situations, which just means describing the types of energy that are present without necessarily describing the specific numbers. So I'm not going to put any numbers on the graph for this one, but I will for some others. So I'm going to say that my bar chart goes up 4 lines and it's all elastic potential energy. And I know that elastic potential energy is contained within the spring. The spring is the reason why the system has that elastic potential energy. I'm now going to imagine that this box is let go. Those little lines next to the box mean that the box is now moving with a velocity that is not 0. And I'm going to imagine that this is a smooth surface, so there's no friction. And what no friction means is that no heat energy, which we here call internal energy, was created. No heat or thermal energy was created as a result of this box moving along the floor. So because there's no more spring energy, and that caused the box to move, and the box didn't gain any height, all of that energy had to go into the box, so I'm going to include that as the other object in my system, and it all went into kinetic energy specifically. So that's what my LOL diagram would look like for this situation. The box started not moving with just elastic potential energy, and after it had only kinetic energy, and the energy went from the spring into the box. Here's example number 2. We can now imagine that the box is compressing a spring still, but it's now facing a ramp. I can see that it does not have any gravitational potential to start off, so all of that energy must still be elastic energy, and it's still contained within the spring. I'm going to imagine that we let it go, and it goes a certain height up the ramp before coming to a stop. So at the end here, I'm going to say that the velocity is 0 again. So what happened here is the elastic potential of the spring went into the box as kinetic energy. Whenever gravitational potential energy appears as a part of our problem, we need to include the thing that is giving our object gravitational potential energy, which here is the entire Earth. And you may be thinking back to the momentum unit where it was really bad to have the Earth in our system of objects. But here in energy, it's actually not really a big deal because we can calculate exactly how much gravitational potential the Earth is giving the object using mgh. So it's totally fine to include Earth in our system of objects in energy, but we can't do it in momentum because it's basically impossible to do momentum calculations with the Earth. But in energy, we just use m times g times h to find how much energy it's giving to an object. So because the change here is still just between mechanical energies, from the elastic potential in the spring to the kinetic in the box to the gravitational potential in the Earth, all the energy is conserved. The total must stay the same. So my final value must also be a bar that goes up 4 lines. And because this box has stopped at a certain height above the ground, it doesn't have any kinetic, so all of its energy must be gravitational potential. We're assuming here again that this is a smooth surface, so there was no thermal energy created by friction, so there's no internal energy on my chart. So all of that energy has gone into gravitational potential. That's what the LOL diagram would look like in example 2. We can move through example 3. We can see that again it's all elastic energy to start, so that means that the spring is in our system. We let the box go, and we're going to imagine that it keeps moving with a non-zero velocity after it gets up that hill. So that hill is not high enough to slow it to a stop. So the box is a part of our system because that's where the elastic potential energy went when it changed into kinetic energy. And the Earth is also a part of our system because the box is now higher. It has a certain amount of height compared to where it was when it started. So that means it has a certain potential to fall back down that height. That's what gives it potential energy, just gaining more height. So I have a problem here because I can't tell exactly how much kinetic compared to the potential it has, and I don't have any numbers to back me up. So that means that I can actually choose for myself what proportion of this object's energy became kinetic energy and what proportion became gravitational potential. There are multiple right answers for these kinds of LOL diagrams that don't give you numbers to calculate. All that I know for sure is that the total has to stay the same. So the total has to still add to 4 lines. So as an example, I could split up those 4 lines into 2 for kinetic and 2 for potential like this. Or I could say it has 3 lines of kinetic and 1 of potential, or 1 of kinetic and 3 of potential. I don't have any way of saying that one is better or worse than the other, so there are multiple correct answers here. This is just kind of eyeballing it.
In example number 4, we can now imagine that this box is compressing a spring aiming straight up. So all of its energy is still elastic, and its energy is contained in the spring. And we can imagine that after it's launched, it rises to a certain height where its final velocity is 0. That means that the energy went into the box as kinetic energy, and then after, the Earth gave it gravitational potential energy. So those are the 3 objects in my energy system again. And at the very end of its motion, it stopped. Its final velocity is 0, so that means that all of the energy went into gravitational potential energy because it's currently at a stop. For example number 5, I'm imagining that we're looking at the same box, but now we're only looking at it when it's halfway up its full potential height. So here its velocity is not 0 yet, it's still moving up. So before, all of its energy is still elastic energy. Because the box is only at half of the total height that it's going to have, and I know that the potential energy is equal to m times g times h, if you cut h in half, that means the potential energy is also cut in half. So I know that at the very end, all of its energy is going to be potential energy. So it's all going to be 4 lines of potential energy. But here, where it's only halfway up, only half of its energy must be gravitational potential, and because it's moving, the other half must be kinetic. So that's an interesting pattern. Whenever an object is up exactly half as high as it's going to go in the vertical direction, half of its energy has been changed into gravitational potential and the other half is still kinetic. Here's example number 6. This is our first example of a rough surface, so there's some friction present. So I'm going to assume that before, this object is moving very fast, so before it encounters this rough surface, all of its energy is kinetic, and that kinetic energy exists in the box. But as the box moves across the floor takes some of its kinetic energy and changes it into thermal energy with friction. So I'm going to include the floor as one of my objects. So afterwards, some of that kinetic energy must have been changed into internal energy, which is thermal energy. And we don't know exactly how much. I'm going to imagine it's just 1 and 3, like this. But if you wanted to say it was 2 and 2 or 3 and 1, that would also be totally fine, because we're not given numbers here. Example number 7 is the first example where we are given numbers. You can see that I'm given a k constant, an initial velocity, a stretch of the spring, and a mass of the object. Using these values, I can see that all of the energy of the box to start off is going to be elastic potential energy. And using the equation 1/2 kx squared, I can calculate the specific elastic potential to be 8 joules. So that means that I'm going to put 8 joules at the top of this graph. And if I put 0 at the bottom, I can easily put the other numbers in like this. So as long as they're even increments, I'm going to say this is 2, 4, 6, and 8 joules, like that. So we can now use these graphs to calculate other missing values in our problems. As an example, I can see that if the hill that this box is going up is 0.1 meters, the gravitational potential energy that it's going to have when it's on top of the hill is equal to its mass times the acceleration of gravity times h, which rounded is equal to 2 joules. So I know that after it climbs this hill, 2 joules of energy will be gravitational potential energy. And because it doesn't have any elastic potential left, the rest of the energy must exist as kinetic energy. So because I know that the total is staying the same, and it starts off with 8 joules of elastic, and there are now 2 joules of gravitational, there must be 6 joules of kinetic energy. And because I know that kinetic energy is equal to 1/2 mv squared, I can actually use that to solve for the velocity. When I do, I find that the velocity is 2.4 meters per second. So that's really exciting to us, because the ultimate goal of physics is to be able to predict motion. And we just predicted the exact velocity of an object moving across a smooth surface, rising a very specific amount, after compressing a spring a very specific amount. And if you do this in the real world, these are the actual values that show up, because energy is really actually conserved, and the way that objects move through the world fits these patterns. Here's example 8. This is the first example of an open system in an LOL diagram. In an open system, the total energy before and after the event can change. So before, I'm going to imagine that this object is not moving and it's on a smooth surface. So I'm going to exclude the person from my system, because the person is kind of adding energy from outside. So I don't really want to consider the energy that's already in the person, because that's chemical energy from the food that they eat, which I cannot account for in these LOL diagrams. So before, the total energy of the box is just 0. It doesn't have any type of energy. And after this person pushes it, it has a certain amount of kinetic energy that it's not going to lose because there's no friction here. So this is what an open system LOL diagram looks like. The total before and after do not have to equal each other.
We can now imagine that this is a very rough surface. So if this is a rough surface, the person pushing on the box is going to be met by a force of friction pushing back against the person. So anytime any kinetic energy is given to the box, it's immediately converted by the floor into heat energy. So after this person pushes this box for a certain amount, all of its energy is going to be heat energy and it's not going to move. This fits another real-world experience. If we start to push an object across a very smooth, slippery surface and let go, the object will continue to move because none of its energy has been converted to heat. But if we push it across a rough surface, it's not going to have any kinetic energy, and so it's not going to move. All of its energy was changed into internal or thermal energy. One last topic to cover in LOL diagrams is elastic and inelastic collisions. In an elastic collision, kinetic energy is conserved. That's actually the definition of an elastic collision. And in an inelastic collision, some energy is lost to heat. So we can imagine that these carts are moving towards each other. So if we add up their total energies, it's going to add up to be some total kinetic energy. And after they impact each other, if they have a perfect elastic collision, that's going to be the same amount of kinetic energy after the collision. However, if we imagine that they have an inelastic collision instead, in example 11, if their energy all starts off as kinetic energy, some of their energy is going to be converted into internal energy. The way to find specifically how much energy was converted is to use the fact that the momentum is also conserved, so you can find the total velocities of the two objects after the collision, and then use that to calculate their kinetic energy. And however much less that kinetic energy is than what they started with, that difference between the initial and final kinetic is going to equal the internal energy. If the two objects come to a perfect stop after the collision, that means that all of their kinetic energy was transformed into internal energy. And that's how you draw LOL diagrams. Obviously, these are very versatile and can describe a lot of very different situations, and you're going to get a lot of practice with them over the next few days. This will be a very quick lecture on force distance graphs. They're a pretty straightforward idea. A force distance graph shows the force applied on an object and the distance the force has been applied for. Because the area under the curve of the graph equals the force applied times the distance traveled, the area under the curve of a force distance graph is equal to the work done on the object. So if I draw a line here, you can see that the area under the curve here is going to be the total force being applied times the total distance, so that'll be equal to d times f, which is equal to work. As a quick example, I'm kind of cheating and just borrowing this example from a previous lecture. The total work here is going to be 4 times 5 times 1/2, which is equal to 10 joules, plus 25 joules, that's the area of that rectangle, plus the area of this triangle, which is equal to 10 joules. And because this force is negative, it's doing negative work, so that's going to be negative 6 joules. So altogether, the total work done on this graph is equal to 39 joules. As a quick example problem, we can say a 5 kilogram cart moves at 10 meters per second. If this graph shows the force applied over the distance the cart is pushed, how fast is it moving after 8 meters of travel? So this is equal to the work. I can see that that work done on the cart is going to be 80 joules, 1/2 base times height. The mass of the cart here is 5, and the initial velocity is 10 meters per second. So that means the initial kinetic energy is 1/2 times that mass times that starting velocity. So that's going to be equal to 250 joules when you put that into your calculator. And the work being done on this is positive 80 joules, so 80 joules of energy are being added because work is equal to the change in energy. So the final kinetic energy of this is going to be 330 joules, so that means that the final velocity, plugging in 1/2 mv squared, the final velocity will be 11.5 meters per second. So that's an example of using a force distance graph in a problem. In this video, I'll take you through an example of a closed system energy problem and an open system energy problem. A big goal in the energy unit is to be able to predict what an object is doing at basically any point, given information about its initial conditions, the values that it starts off with at the beginning of the problem, and using the idea that in a closed system anyway, the total energy remains the same. So I've made 5 columns to figure out the kinetic, gravitational potential, and elastic potential energy at each of the 5 points along this track for this ball, and also a row for the total energy at each point. One of the big ideas in these types of problems is that if I can figure out the total energy at any one point along this track, I'll know the total energy everywhere because this is a closed system. because the only transfers are happening between mechanical energies, so the total energy is remaining the same. Starting with position number 1, we have a mass of 5 and a velocity of 0 meters per second, 4 meters above the ground. Right away, I can see that because it's not moving, it doesn't have any kinetic energy at position number 1, and it doesn't have any elastic potential either because there's no spring being stretched or compressed. So the only type of energy it must have is gravitational potential energy. And I remember that the equation for gravitational potential energy is m times g times h, mass times 9.8 times the height. So when I multiply out 5 times 9.8 times 4, I get 196. So the gravitational potential at point number 1 is 196 joules. And I can see now that the total energy is going to be those three things added together, and 0 plus 196 plus 0 is just 196. So the total energy at that first point is 196 joules. And because there's no energy coming into the system or leaving the system, just transformations of mechanical energy, the total energy must stay the same at every other point. So I'm going to use this fact to predict the ball's velocity at point 2, 3, and 4, and then predict how much the spring will be compressed by at point number 5. And the big central idea here is that the only piece of information I needed for this was the ball's initial conditions, the values that it's starting off with at the beginning of the problem. So I'm going to let it fall, and it gets faster and faster until it hits point number 2, and it doesn't have any height left to fall, and we want to figure out its velocity. So right away I can see it doesn't have any spring potential because there's no spring, and it doesn't have any height left, so that means that its gravitational potential is also 0. So that means the only type of energy it can have is kinetic, and we can see that the kinetic plus the potential plus the spring is 196 joules. So that means that the kinetic is also 196. And I can use this in my equation, kinetic energy is 1/2 times the mass times the velocity squared, to solve for the velocity of the ball here. And when I do that, I find that the ball is moving at 8.9 meters per second. So that's really cool. Just using that information from point number 1, we can predict exactly what the velocity of the ball is going to be at point number 2. And we can keep going as this ball goes around this loop-de-loop up to the top where it's at position number 3, and we want to know its velocity here. So here I can see that again there's no elastic potential, but it does have some gravitational potential because it now has a height that it can fall. Gravitational potential is mgh, so that's going to be 5 times 9.8 times 3, because the height here is 3 meters rather than 4. Plugging that in, I get 147 joules. Based on that idea, I can see that kinetic plus 147 equals 196, so the kinetic energy must equal 49. And I can use 1/2 mv squared to find that if 49 joules is equal to 1/2 times 5 times v squared, v by itself is equal to 4.4 meters per second. So again, that's pretty cool. We know that if it goes up this loop-de-loop, at the very top, it has to be moving at exactly 4.4 meters per second if the loop-de-loop is exactly 3 meters high. We can now let this fall and then go up this hill to position number 4. So the hill must slow it down a little bit, which makes sense because it's having some of its kinetic changed into gravitational potential, but there's still no spring potential. So there's a 0 there. Solving for the gravity here, that's going to be 5 times 9.8 times 2, which is equal to 98 joules. So we know that kinetic plus 98 equals 196, so the kinetic must also be 98. Solving for the velocity here gets me 6.3 meters per second. And for this last part, I'll predict exactly how much this spring will be compressed by before the ball stops moving. So one thing I notice right away is that this ball still has a certain height. It's still above the point that we defined as being 0 back at position number 2. So if it still has the same height as in problem number 4, it must still have the same gravitational potential energy as problem number 4. So it still has 98 joules of gravitational potential energy. And we know that it's coming to a stop, so there's 0 joules of kinetic energy. So all that's left over must be elastic potential. So 98 plus elastic equals 196. So elastic potential is equal to 98. Plugging this into my elastic equation, I can see that the stretch must be 0.7 meters given that k is equal to 400. I wrote that just below the spring. So that is the final stretch of the spring. So that was pretty cool. We could get all of that information about the ball's velocity at different points with 100% certainty, only using the fact that the ball started with a certain height and a certain velocity and a certain mass. Everything else just followed from that. And even if I blocked off certain parts of the problem, as long as you had the fact that the ball goes up a certain amount of height again and then hits that spring,
That's enough information to figure out how much the spring is stretched or compressed by. So one really fundamental idea in physics as a whole that energy is an especially good example of is that in a lot of these types of situations, the only thing that matters is the initial condition, the starting variables of the problem. Everything that happens in the middle doesn't affect what happens next as long as it's a closed energy system. Another kind of mind-blowing thing is that I can actually rewind this and assume now that the ball is being launched to the left by a spring of k constant 400 that's compressed by 0.7 meters, and all the velocities will actually still occur just in the opposite direction until it gets to a final height of exactly 4 meters at position number 1 before coming to a stop. And then it can go back and forth forever, assuming that it's not losing any energy from the system. So there's a certain symmetry there. I can now do something similar but with an open system. I've set up a situation where there's a certain rough spot on the floor that's going to have a certain amount of friction. Specifically, the coefficient of kinetic friction here is going to be 0.3, and the rough spot is 10 meters long. I'm also going to imagine that this ball is starting at 10 meters in height. So it starts off with no kinetic and no elastic potential because it doesn't have any movement or any spring. And when I calculate the gravitational potential, I get 490 joules. So that means that the total energy is 490. But that's only going to stay the same until it encounters that rough patch. So it'll be okay at position 2, but it'll be different at position 3, because that's after the work will apply on it that will turn kinetic energy into heat energy. I can see that at the bottom, it's not going to have any gravitational potential left. So now all of that 490 must be kinetic energy. Solving for kinetic energy there gets me 14 meters per second. We can now imagine that it rolls across this surface. And if it's rolling across this surface, it must have a force of friction acting in the opposite direction. And I know that the force of friction is equal to the coefficient of friction times the normal force. Using my equations for the force of gravity, I can see that the force of gravity is 49, so the normal force here must also be 49 to balance that out. So using that coefficient times the normal equals the friction equation, I get that the friction here is 14.7 newtons. So the work done by friction is going to be that force, 14.7, times the 10 meters that it was applied for. And it's pointing in the opposite direction of the ball's displacement, so that must be negative. So it's negative 147 joules. So if that's doing negative 147 joules of work, the ball loses 147 joules of kinetic energy to heat energy in that time. So the total energy after is going to be 490 minus 147, which is equal to 343 joules. And again, here there's no potential or spring, so that means that there are 343 joules of kinetic in this ball. And you can see that that means that the ball is now moving at 11.7 meters per second. If you solve that same problem with kinematics using the same force and displacement, you would actually get the same result. If it started with 14 meters per second and had that force applied on it for that distance with its mass, it would come out to be exactly 11.7 meters per second. We can now calculate how far it will go before coming to a stop back up the hill, because the total energy is still 343, and there's no elastic potential or kinetic at the top because it's coming to a stop, so the potential is 343. Solving for the height using 343 equals mgh gets me a final height of 7 meters. So that's how high the ball would go as a result of having that friction applied on it.
This video is going to be about the idea of power in physics, which has a pretty similar definition to our everyday use of the word power. In physics, power is a measurement of a change in energy per time, so it's a rate of change of energy per time. It's measured in units of watts, which actually just means joules per second, because again, it's energy per time. And like energy and work, power is a scalar. Power supplied to an object is also equal to the force applied to an object times the velocity of an object. The force times velocity definition of power isn't used quite as much as the energy per time definition, but it does come up every now and then, and in this video I'll show you why it looks the way that it does. Just as an example, you've probably seen that light bulbs are often labeled with the power that they use. For example, a 60-watt light bulb uses 60 joules of electric energy per second. So that's what a watt means. A watt is a joule per second. So a 60-watt light bulb uses 60 joules of electric energy every second. So if I write that equation, power is equal to the change in energy per time, we can see that a 60-watt light bulb will use 60 joules of energy in 1 second, or 120 joules of energy in 2 seconds, or 180 joules of energy in 3 seconds, or 240 joules of energy in 4 seconds. So power is a description of the rate of change of energy per time. Here's an example problem with this idea of power. How much energy will a 60-watt light bulb use if left on for 8 hours? So here I'm going to start by writing down my given variables, and I know that I'm given the power is 60 watts, and I'm also given that the time is 8 hours. And because the standard unit of time in physics is seconds, not hours, I'm going to need to convert that down to seconds. And when I do that, I find that this is 28,800 seconds. And we're trying to find the change in energy of the light bulb. If power is change in energy divided by time, that also means that power times time equals the change in energy, which is what we're trying to find here. So plugging that in, 60 watts, which means 60 joules per second, times 28,800 seconds will equal the change in energy. So our final answer is 1,728,000 joules of electrical energy. So that's quite a bit of energy used in just one day by a 60-watt light bulb. Moving on to example problem number 2, a car engine accelerates a 1,000-kilogram car from rest to 20 meters per second in 4 seconds. How much power does the engine use? So we're given time right off the bat, that's 4 seconds, and we're trying to find the power used by the car. But we're not given the change in energy here, so we're going to have to calculate that. I can see that the type of energy that's going to be involved in this situation is kinetic energy, because we're given the car's mass and the car's velocity. I can see that the type of energy that's going to be present in this problem is kinetic energy, because we're given the car's mass and the car's velocity. So I can calculate how much kinetic energy it starts with, how much kinetic energy it ends with, and the difference between those will be equal to the change in the energy. If it's starting from rest, it's just going to be 1/2 times the mass times v squared, and v here is 0 because it's not moving. So that's just 0 joules. And the final kinetic energy of the car is 1/2 times 1,000 kilograms times 20 squared, which is equal to 200,000 joules. So the change in energy here is 200,000 joules. So we would say that the power is the change in energy over time, which means that it's equal to 200,000 joules over 4 seconds, which means that this car's engine has a power of 50,000 watts. Moving on to example problem 3, a crane lifts a 100-kilogram crate straight up at a constant rate of 5 meters per second. How much power does this require? I'm actually going to solve this one in 2 different ways. The first way we'll use the power is equal to energy divided by time equation, and the second one will use the force times velocity equation. To solve it the first way, I'm going to need to know how much the energy is changing by, and since this thing is gaining potential energy, I'm going to need to know how much height it gains in how much time. And if it's going up at a constant rate of 5 meters per second, that means that it's going to go up 5 meters in exactly 1 second. So that's the height I can use and the time to calculate the change in energy and the time to find the power. So the time is 1, and the starting potential energy of that box is just 0 because it has a height of 0, and the final potential energy is going to be its mass times gravity times height, and its height is 5 meters, so multiplying that out gets me 4,900 joules, so the change in energy is 4,900 joules. And the power there is 4,900 joules divided by 1 second, which is equal to 4,900 watts. So that's the way of solving it with the change in energy over time equation. To use the force times velocity equation, I can see that the force of tension that will be required from the crane to lift this box at a constant rate is just equal to the force of gravity. It just has to balance out the force of gravity going down. So I can see that the force from the crane is 980 joules, and the velocity is 5 meters per second. Using that equation, power is equal to force times velocity. I just multiply out the force and the velocity, and I get the same answer as I got in the previous problem, 4,900 watts. This equation is meant to show you the connection between the two equations above my head. You can see that even though they're written differently, they're actually implications of each other. If power is actually change in energy divided by time, that's also equal to the work done divided by time, because work is change in energy, and because work is force times displacement, power is equal to force times displacement over time. And because displacement over time is equal to velocity, we can replace the displacement over time in that equation with velocity. So we just get force times velocity as another equation for power. And that's everything that you need to know about the definition of power. The idea of efficiency in physics is another idea that's pretty similar to how we use it in our everyday lives. The definition of efficiency is the ratio of how much useful energy or power we get out of a system versus how much energy we put into the system. It can be expressed as a number between 0 and 1, or a percentage between 0% and 100%. It does not have a unit because it is a division of two identical variables, two types of work or energy or power. So efficiency is the useful work out over the total work in, or the useful power out over the total power going into the system. Just to show you that these two things are equivalent, the power out over the power in, because power is equal to work over time, is equal to the work out of a system over the time divided by the work going into a system over the same time. And if we cancel out the time, that's just the useful work out over the total work in.
You might ask yourself, how do we know which power coming out of a system counts as useful? And that is kind of subjective. It's based on how we're looking at the problem and what we want to get out of the situation. As an example, the average incandescent light bulb has an efficiency of just 5%, or 0.05. This means that 5% of the electrical energy we put into the light bulb is converted into useful energy. And because this is a light bulb, when we use it, we usually want to get light out of it. So we consider the useful energy to be whatever radiant energy or light energy we get out of this machine. If it's just 5% efficient, that means that 5% of the electrical energy that goes in gets turned into radiant energy, the stuff that we want, and 95% leaves the bulb as useless energy. In this case, it leaves it as heat specifically. Whenever we use an incandescent light bulb, no matter how much electricity we're putting into it, only 5% comes back to us as useful radiant energy, and the rest is lost as heat to the environment. As an example, if an incandescent bulb is a 60-watt bulb, that means that 60 watts of electrical energy are going into the bulb, but only 3 watts of useful radiant energy, just 5% of that 60, are coming out of the bulb as radiant energy, and the rest, the other 57 watts, 95% of the energy, is coming out as useless thermal energy. And again, what counts as useful energy really depends on the situation and what we want to do with the device. For example, in cold weather, we do want our homes to be heated, so thermal energy is useful to us. And in this case, we could possibly say that the light bulb could be understood as 100% efficient because all of the energy is useful and valuable to us. So what counts as useful energy is kind of subjective and based on the problem that you're trying to solve with the machine. Just as a note, lost or useless power or work is usually thermal energy. When we talk about that, we usually mean heat leaving a system. This is not always true, but it can be assumed when it's not clear where the energy is going. Here are a few example problems. In this first one, a forklift uses 10,000 joules of electrical energy to lift a 50-kilogram box 5 meters. What is the efficiency of the forklift? We know that the total work in is equal to 10,000 joules of electrical energy. It's using 10,000 joules of energy to perform this task. And I can see that the change in potential energy as it lifts the box is going to be from 0 to 5 meters, so the change is just going to be the potential energy that this box has at 5 meters, which is 50 kilograms times 9.8 times 5, just mass times gravity times height, which is equal to 2,450 joules. So that's how much energy this forklift was able to turn into useful energy, the good type of energy that we want in this case, which is gravitational potential energy. Like a forklift is designed to give objects gravitational potential energy. So that means that the useful work out is also 2,450 joules. Because the efficiency is the useful work out over the total work in, that's going to be 2,450 over 10,000, which is equal to 0.245 or 24.5%. To convert between a decimal and a percentage, you just multiply or divide by 100. What this is saying is that this forklift is 24.5% efficient. Whatever energy you put into the forklift as electrical energy, it's going to be able to use about 24.5% of that energy as useful gravitational potential energy. The rest of the energy is probably lost to heat in the engine of the forklift. We can do another example problem. A 60-watt light bulb that is 5% efficient is left on for 4 hours. How much thermal energy is created by the light bulb? I'm going to start by rewriting the 5% as a decimal because that's a little easier to do math with. 5% is equal to 0.05 when written as a decimal. I know that 0.05 is equal to the efficiency, so that's equal to the useful power out over the total power in, and I know that the total power going into the system is 60 because it's a 60-watt light bulb, so that 0.05 is equal to the useful power that we're getting out of the light bulb divided by 60. Using that setup, I can find the useful power that we're getting out of this light bulb. I can see that that's 0.05, remembering that efficiency doesn't have a unit, times 60 watts, which is equal to 3 watts. But that's not what the question is asking about. It's asking about how much thermal energy is created by the light bulb. If this light bulb really is 5% efficient, that means that when we put 60 watts in of electrical energy, we get 3 watts of radiant energy out, so the rest must be thermal energy. So that means that it's 57 watts of power that's going into thermal energy specifically. And 57 watts of power means 57 joules of energy created every second. We can now solve the problem of how much thermal energy was created in 4 hours, because we know that it's generating 57 watts of thermal power, which means that it's generating 57 joules per second of thermal energy. So that's the power that exists for thermal energy, and this is the time, and we need that in seconds because physics always measures time in seconds. Multiplying that out gets me 14,400 seconds. And power is the change in energy over time, so plugging that in, 57 watts is equal to the change in energy over 14,400 seconds. Therefore, the total thermal energy created by this 60-watt light bulb in 4 hours is 820,800 joules. It's pretty mind-blowing that a small household light bulb like that can create so much energy.
Moving on to problem number 3, an 800 kilogram car's engine is 30% efficient. If we want to accelerate the car from 10 meters per second to 20 meters per second, how much chemical energy from the gas do we need to use? So I remember that work is equal to change in energy, and here I need to know the starting and final kinetic energy of the car, because we're changing the energy in some way, and that additional kinetic energy is the good, useful energy I'm trying to get out of this system. The starting kinetic energy of the car is 1/2 times its mass times its velocity squared, which is equal to 40,000 joules. The final kinetic energy is 1/2 times 800 times 20 squared, which is equal to 160,000 joules. So the change in energy is 120,000 joules. So that's how much useful energy is being added to the system. So the useful work out is 120,000 joules. And because the car is 30% efficient, I'm going to rewrite that as a decimal, which is 0.3. Plugging that in, 0.3 is equal to 120,000 joules over the total work in. So the total work in is equal to this number, which is equal to 400,000 joules. Just to repeat, if a car's engine is 30% efficient and you want to make it accelerate from 10 meters per second to 20 meters per second, you're going to have to put in 400,000 joules of chemical energy from the gas to give it that 120,000 joules of extra kinetic energy.
This lecture is going to be about the difference between temperature, internal or thermal energy, and heat. These are words that all seem very similar to each other, but all have very different, very specific definitions. Before we talk about these three ideas, I need to talk about the kinetic theory of matter, because this is a concept that's going to be guiding our entire understanding of basically this entire unit of material. Everything that we talk about will tie back to this central concept. All matter is made up of a large number of tiny particles, and the microscopic or small behavior of the particles determines the macroscopic or large behavior of the material. As an example of what I mean by the kinetic theory of matter, we can compare ice and water with each other, and I know that ice and water are the same fundamental thing. They're both made of H2O, but ice and water have different temperatures and different properties. Ice feels very cold, it's a solid, and water feels probably warmer, and it's a liquid. Now, I know that these two things are fundamentally the same as each other. They're both made of H2O. So I want to know where the difference comes from. Why is it that ice is a solid and feels cold, and water is a liquid and feels warm? And the only difference, the only physical difference that's causing these two things made of the same material to behave differently is the behavior of the very, very tiny particles like the molecules that make these objects up. If we were to zoom in, like I'm showing in the black boxes, and observe what the particles in each material are doing, we'd see something like this. In the ice, the particles that make it up are all kind of stuck together and shaking, but just a tiny little bit. They have just a little bit of motion as they move back and forth around each other. The overall structure doesn't really change its shape. And in the water, I can see that the particles are much more free to move around in random directions, but still stay kind of close together, but they're moving a lot more as well. So when we experience temperature, when we experience something as being hot or cold, that's actually just our brain signal telling us how much these particles are moving. And when we experience something as being a solid or a liquid, all that really is how much the particles are able to hold each other together. If they're able to hold each other together very strongly, you can see they behave as a solid, and if they can't really hold each other together, they behave as something like a liquid. So this big idea is going to be guiding the entire unit. The macroscopic or large behavior of objects in terms of temperature and heat really depends on the small movements of the small particles that make these objects up. There are three words in the subject that appear to be very similar, but all have different meanings. Temperature, and then either internal energy or thermal energy, whatever you want to call it, and heat. Temperature is a measurement of the average kinetic energy per particle in a material. Its variable is capital T, and we measure it in degrees Celsius or Kelvin. Internal energy or thermal energy is a measurement of the total kinetic energy of particles in a substance, plus the total potential energy of the bonds between the particles. Its variable is E int, and the unit is J, or the joule, because it's a form of energy. Heat is the total change in thermal energy, or the final thermal energy minus the beginning thermal energy. So heat is a change in energy, and we use the variable capital Q to symbolize heat. And because it's a change in energy, it's also measured in units of joules. So what's the difference between temperature and internal energy? They seem very similar to each other. Temperature is the average kinetic energy per particle, and internal energy is the total internal energy of all the particles in the material. Intuitively, those two things don't sound too different from each other, so I'm going to give you a few intuitions about the exact definition of temperature and internal energy and how they're different from each other. I'm going to imagine that we have two materials, one on the left and one on the right, and I can see the particles in the material. And I can also see how much kinetic energy each particle contains. So I've written that in the center of each particle. The temperature is the average kinetic energy per particle. So to find that average for the material on the left, I can just add the total kinetic energy and divide it by the number of particles. So I can see that this material has an average kinetic energy of 3 joules per particle. On average, of the 2 particles, each one has an average of 3 joules. So that would be a way of recording the temperature. The internal energy is the total energy that exists in the material. So the total energy here would just be 6 joules. So that's a way of understanding the difference between temperature and internal energy. Temperature is an average energy per particle, and internal energy is just a total sum of the energy that you have in a material. If we look at the material on the right, and we find its average kinetic energy per particle, I find that that's actually also 3 joules per particle. So these two materials actually have the same temperature as each other because they have the same average kinetic energy as each other. But their internal energy is very different. I can see that the internal energy of the material on the right is much greater than the internal energy of the material on the left. So these two sets of particles have the same temperature, but different internal energy. So this is one way of showing the difference between what we mean by temperature and what we mean by internal or thermal energy. Another example could be a heated pool where we have a lot of hot water inside. We take a bucket and take just a little bit of hot water out of the heated pool. Because the particles in the bucket are on average moving in the same way as the particles in the pool, I would assume that the temperature of the pool is the same as the temperature of the water in the bucket. But because there are so many more particles in the pool than in the bucket, those particles must in total have more energy than what's contained in the bucket. There's more total thermal energy in the pool than there is in just the little bucket, and so we would say that the energy in the pool is greater than the energy in the bucket. So that's another way of understanding the difference between temperature and internal energy. This last note that I'm going to make is a little complicated. We're going to talk about it a lot more in future videos. Temperature is only affected by the kinetic energy in particles, but internal energy is a measurement of both the kinetic and potential energy of particles. Potential energy exists in the bonds between the particles holding them together. We'll focus on this more in the phase change and temperature versus heat graphs lectures later in this series. So just as an example, we can make a graph of the kinetic and potential energy of a material. It looks a little weird. It looks like this. I'll explain why that is in a future video. But if I begin to change the kinetic and potential energy, you'll notice that the temperature is only affected by the kinetic energy, and when I change the potential energy, that changes the bonds between the particles, but it doesn't change the temperature. So temperature is only a measurement of the kinetic energy in a material, whereas the internal energy is a measurement of the total amount of potential and kinetic energy together. So again, that's a little complicated. You just have to remember that that difference exists, and I'll go into that in more detail in future lectures. There are 3 common units for temperature, and we only use 2 of them in science: Fahrenheit, Celsius, and Kelvin, and we only use Celsius and Kelvin when we're working in science. These have just been adjusted to make more sense scientifically. The table on the left shows some important temperatures on each scale. You can see that we have the lowest possible temperature that can be reached on each scale, the temperature at which water freezes, and the temperature at which water boils. On the right, I have a table showing ways of converting from each unit of temperature to each other unit of temperature. Notice on the chart that a change in 1 degree Celsius is equal to a change of 1 degree Kelvin. When you go up 100 degrees Celsius on the left, you also go up 100 degrees Kelvin on the right. This will matter when we're doing math with temperature. A change in temperature in terms of Celsius is always equal to a change in temperature in terms of Kelvin. They're always the same number. The kinetic theory of matter says that what we experience as temperature is actually just the average kinetic energy of particles. This means that there's a lowest possible temperature an object can have, a point where all the particles inside it have no kinetic energy at all and are not moving. We call this temperature absolute zero. But it's physically impossible to actually get to absolute zero just because of some other laws of the universe. But if we could get to absolute zero, the picture on the bottom right is what it would look like. All the particles just completely frozen in place. Because it's not possible to have less motion than no motion, it's not possible to have less temperature than the absolute 0 point of temperature. So you can see that that's 0 degrees on the Kelvin scale. That's actually how the Kelvin scale was developed. It started from a point of absolute 0. It's negative 273 on the Celsius scale and negative 459 on the Fahrenheit scale. So there is a lowest possible temperature that you can reach. Absolute zero temperature does not occur anywhere on Earth or actually anywhere in the universe, and this means that even very cold material still has some internal energy. This can be a little confusing for students because they don't normally think of cold things like snow as having thermal energy. They usually only think of hotter things like burning wood or lava or something like that as having thermal energy. But actually, as long as a material is not at absolute zero, that means that its particles are moving a little bit, which means that there's still some internal thermal energy. So even very cold material like snow has that internal energy. And it's actually possible for a lot of cold material to have more total internal energy than a little hot material. If we were to compare the total internal energy in all the snow on Mount Everest, as an example, and compared that to the internal energy of wood in a fire, we would actually find that the snow had more internal energy in total, because if we were to add up all the small amounts of kinetic energy in all the little bits of snow in the mountain, that very large amount of very small quantities would actually add together to be more than the small amount of large quantities of kinetic energy in the wood. So even though the particles in the wood are moving much faster than in the snow, there are so many more particles of snow that the total internal energy is greater in the snow than in the fire. Now that we've addressed temperature and internal energy, the last subject to talk about is heat. Heat is the change in thermal energy, and because work is another name for the change in energy, heat can also be described as the thermal work done by or on a system. This has its own name and symbol because thermal energy often changes and moves from one object to another, so we need a specific mathematical symbol for that because that's going to come up a lot in very specific equations. As an example, if the blue object had 100 joules of internal energy and the green object had 40 joules of internal energy, and we imagine that we transferred 20 joules of energy from the blue object to the green object, the heat emitted by the blue object and gained by the green object would be 20 joules. And so the blue object would be reduced by 20 and the green would be increased by 20. Because energy is conserved, which means it cannot be created or destroyed, the heat emitted by one object must be the same as the heat gained by the object receiving it. So if we imagine that we're giving heat from object 1 to object 2, I know that the heat lost from object 1 will be equal to the heat gained by object 2. Just going back to our other example, in this example 20 joules were lost from the blue object and gained by the green object, and I can see that that makes the equation on the bottom work. So that's everything that you need to know about the difference between temperature, internal energy, and heat. These are the definitions, variables, and units again. And just remember that all our understanding of this material comes from the central idea of the kinetic theory of matter, which says that, again, matter is made up of a large number of tiny particles, and the microscopic behavior of the particles determines the macroscopic behavior of the material. This will come up a lot as we begin to explore this topic more in the next few videos. This lecture is about phase changes. Before we start talking about phase changes, I need to talk again about the kinetic theory of matter, because again, this is the theory that's guiding all our understanding of what's happening in most of this unit, and this is going to matter a lot for the idea of phase changes as well. Again, the theory says that matter is made up of a large number of tiny particles, and the microscopic small behavior of the particles determines the macroscopic large behavior of the material. What we're looking at in this lecture is how the same material, like H2O, can exist in different states like a solid or a liquid or a gas, and what that really means for it to exist in those different states. You can see here that when a material is in its solid state, what's happening to its particles is that they're all kind of stuck together. They still vibrate and have some random kinetic energy, but they don't really change their arrangement. They're kind of being held in place by each other. And when the same material is a liquid, you can see that the molecules are not really holding each other together quite as well as they were before. They're still staying together, they're still in some ways kind of stuck together, but they're much more free to move around. So the same physical material can have very different properties based on how its particles are being held together. And we call these different properties phases of that same material, or a phase of matter, a state in which the matter can exist. We're only going to worry about 3 phases in this unit: solids, liquids, and gases. You've almost definitely heard of these before, but there may be some properties of solids, liquids, and gases that you don't know about. I'm going to have you take a minute to fill out this table in your notes, and just take down any important information you can see. Notice that in the micro view for the 3 phases, the particles are being held together in different ways. In the solid, they're being held together very strongly. In the liquid, they're still staying relatively close to each other, so they're still holding each other together in some way. And in the gas, they're just free floating and not holding each other together at all. You may also notice that the kinetic energy increases as we go from solid to liquid to gas. They're moving more and more as we go down that list. The bonds between the molecules are becoming weaker. They're holding each other together less and less strongly, until in the gas, there's no bonds between the particles at all. The space between the particles gets larger as they go, And there are certain noticeable properties of solids, liquids, and gases that can help us identify which one is which. So just as an example, these are the phases of water. Its solid phase is ice, its liquid phase is water, and its gas phase is steam. You'll notice that as we go from solid to liquid to gas, the average kinetic energy of the individual particles is increasing. Each individual particle is moving faster in liquid than it is in solid, and faster in gas than it is in liquid. This means that the temperature increases as we go from solid to liquid to gas, because temperature is literally just a measurement of the average kinetic energy. And this fits our intuition. We normally associate liquid water as being warmer than ice, and steam as being warmer than liquid water. We're now on the main focus of the lecture. A phase change is a way that matter changes its phase from one to another. Each specific phase change has a name that you will have to memorize for this unit. So I'm just going to run through each one and give you an example of each. Going from solid to liquid is called fusion. The more common name for that is just melting. Going from liquid back to solid is freezing. Going from liquid to gas we call vaporization. A more common name for that is just evaporation. Going from gas back to liquid is condensation. So if you've ever had a cold drink like a soda on a hot day, when the gaseous particles of water in the air impact your cold drink, the drink is cold enough to convert that gas back into a liquid, and so the outside of your drink becomes wet. It's also possible to go straight from a solid to a gas. We call that sublimation. And it's possible to go from a gas to a solid. We call that deposition. So again, you will need to memorize these 6 names for the different phase changes. The particles in a material have an average kinetic energy and an average potential energy. The potential energy is the energy of the bonds holding the particles together. During a phase change, only the average potential energy changes. The average kinetic energy does not change during a phase change, so the temperature does not change during a phase change. I'll address that more in an animation in a minute. Before, I need to talk a little bit more about potential energy. We record the binding potential energy between particles as negative because we need to add energy to the particles to remove their bonds and get the binding energy to 0. For example, if these particles existed in a liquid, and it required a total of 10 joules to heat that liquid to a solid, we would say that the bonds between the particles contain negative 10 joules of energy because it would require an additional 10 joules of energy being added to it to remove those bonds, turn it into a gas, and get the total energy in the bonds to 0 because there are no more bonds between the atoms at all. So one more time, this is basically just a notation trick where we can say, oh, because we need to add some energy to this material just to get those bonds to 0, we can record it as containing this negative energy that we can cancel out and remove the bonds that way. So potential energy is recorded as negative when there are bonds between the particles. Going back to solid and liquid and gas, solids have very strong bonds, so that means that the particles in solids have very negative potential energy. Liquids still have bonds holding their particles together. The particles just don't float off into random directions, but the bonds are less strong than solids, and so they contain less negative potential energy. And in a gas, there are no bonds between the particles at all, so that means there's no potential energy between the particles. So even though there's no potential energy in a gas, gas actually has the most potential of any of the phases because the other 2 phases have negative potential energy, and 0 is a higher number than negative numbers. So there's more and more potential energy as we go from solid to gas, even though gas has no potential energy. That can be a little counterintuitive and take a little getting used to. So fusion adds potential energy, and vaporization also adds potential energy because it's adding in energy to remove those bonds. And condensation subtracts potential energy, and freezing also subtracts potential energy because that's taking energy out and making the bonds between the particles stronger. And sublimation also adds potential energy, and deposition subtracts potential energy. The phase of a material only changes at very specific temperatures. The melting point of a material is the temperature at which the phase changes from solid to liquid. The melting point is also the temperature where liquids change back into solids. And the boiling point of a material is the temperature at which the phase changes from liquid to gas, or vice versa. The boiling point can also be where gas condenses back into a liquid. As an example, the melting point of water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. When a material is not at its melting or boiling point, energy added to it changes its temperature, the kinetic energy of the particles. When a material is at its melting or boiling point, energy added to it changes its phase, the potential energy in the bonds of the particles. This can be a little complicated, so I'm going to give you an animation of the total energy contained in ice as we continuously add heat to it over time. And I'm going to pretend that the ice is starting at absolute 0, so it starts off with no kinetic energy at all. And because ice is a solid, that means that there is a lot of negative potential energies. So you'll notice that on the graph, the purple line representing potential energy is very negative. It's very below the 0 point, and it's at the point where the material is a solid. You'll also notice that I have a picture representing the bonds between the particles. They're very strong right now because it's a solid, and I have a thermometer showing how the temperature increases as the kinetic energy increases. So I'm going to start to add energy at a constant rate to this material. Because the material is not at its melting point, all the energy that's added to it goes into changing the kinetic energy and the temperature, not the phase. The phase only changes at the melting and boiling point, and if it's not at that point, all the energy goes into changing the temperature instead. So it continues to add and change the temperature until the exact moment when the material reaches its melting point and it has some kinetic energy. As soon as it reaches its melting point, the energy that I'm adding to this continuously stops going into changing the kinetic energy and starts going into changing the potential energy instead. The energy that I'm continuously adding to it now goes into adding potential instead of kinetic and changing its phase. And you'll notice that the bonds between the particles become weaker until the material is a liquid. And at the exact moment when the material has become a liquid, it stops melting. And all the energy that I'm adding goes back into changing the temperature instead because it's done changing its phase. So once it's finished changing its phase and it's completely in its new phase, it's no longer melting. So all the energy adds kinetic energy and continues to add kinetic energy, which increases the temperature until the temperature reaches the boiling point of the material. And the boiling point is the other place where the material changes phase instead of temperature. So now all the energy is going to go into changing phase instead of temperature. This time the material is evaporating or vaporizing, or going through vaporization if we want to use the technical term. So the energy that I'm adding now is being used to cancel out that negative potential energy and remove the last of the bonds between the particles until there are no bonds left. And when that happens, the material has been completely changed into a gas, and now any additional energy I add to it will add into its kinetic energy and continuously increase its temperature instead of changing its phase, because there's no other phase for it to change into now. So any additional energy I add will just add more kinetic energy and cause the temperature to increase. That was a lot. We're going to be circling back to this concept in the next few videos as we get a better and better idea of how to describe this process. But it's really important that you have that overview of what's happening, where a material only changes its phase at the melting or boiling point, and all the energy added goes into changing its phase. And anywhere outside of those two very specific temperatures, all the energy goes into changing the temperature rather than the phase. So again, we'll keep circling back to this in the next few videos. Just one last thing to note, the specific heat of a material changes based on the phase it's in. This means that different phases of matter require different amounts of energy to change their temperatures. So we know that water can exist as ice, liquid, and steam, and these are the specific heats of each. So you can see that ice has a specific heat of 2,100 joules per kilogram degree Celsius, water has a specific heat of 4,200 joules per kilogram degree Celsius, and steam has a specific heat of 2,000 joules per kilogram degree Celsius. And you'll see I've also written out those physical meanings in words. So that's the basics of what you need to know about phase changes. In the next lecture, we'll learn a new equation to understand exactly how much energy is required for a material to undergo each specific phase change. This lecture is about specific heat and how to use the concept in equations. Specific heat is a measurement of how many joules of heat are required to change the temperature of 1 kilogram of mass by 1 degree Celsius or 1 Kelvin. Remember that those changes are the same. So the equation for specific heat is the heat required to change the temperature divided by the mass of the material multiplied by the change in temperature in degrees Celsius or Kelvin. This equation on its own can be a little confusing, so I'm going to give you some intuitions with some animations on the bottom in just a minute. Just be aware that this equation is more often written as the much more well-known Q equals mc delta T. I've written that on the top right, but that equation really just comes from the definition for specific heat. So again, a material-specific heat tells you how many joules are required to change the temperature of 1 kilogram of that material by 1 degree Celsius. So as an example, we can pretend that this blue material in the bottom center has a specific heat of 50 joules per kilogram degree Celsius. This means that for every 1 degree Celsius that we want to change, we have to add or subtract 50 joules of energy per kilogram of the material present. So I'm going to give you this visual in the bottom center showing you what's happening as we change the heat, and I'm also going to have this equation written out on the bottom right showing you how the math of what's happening fits together in that equation. So a specific heat of 50 joules literally means that if we add 50 joules of energy to 1 kilogram of the material, that's going to result in a temperature change of 1 degree. So if it requires 50 joules to change the temperature by 1 degree for every 1 kilogram that we have, and we only have 1 kilogram, if we add 100 joules, that's twice the amount needed to change the temperature by 1 degree Celsius. So that means 100 joules would change the temperature by 2 degrees Celsius. And you can see that that math works out on the right. If I were to add 200 joules to just 1 kilogram of this material, that's 4 times the heat required to change the temperature by 1 degree. So that means that 200 joules would change the temperature by 4 degrees. Let's say that we had more of this material. Suddenly we have 2 kilograms. The specific heat says that 50 joules are required to change the temperature of 1 kilogram by 1 degree. So now we're trying to change the temperature of twice that mass. So if 50 joules is enough to change 1 kilogram by 1 degree, it's only going to be enough to change 2 kilograms by 1/2 of a degree. We now have twice as much mass to change, so that energy is kind of evenly distributed to both, so each individual 1 kilogram only gets 25 joules, which is only enough to change the temperature by 1/2 of a degree. So because this is 50 joules per kilogram degree Celsius, if we want to change 2 kilograms by 1 degree, and this material requires 50 joules per kilogram to change its temperature by 1 degree, if we have 2 kilograms, we need 100 joules just to change its temperature by 1 degree Celsius. So in general, because the specific heat is 50 joules per kilogram degree Celsius, and we have 2 kilograms, it requires 100 joules to change this material by 1 degree Celsius. So if we were to add, say, 300 joules to the material, that would only change the temperature by 3 degrees Celsius. This equation is pretty easy to use. I'm just going to do some example problems. Water has a specific heat of 4,186 joules per kilogram degree Celsius. If you're trying to heat 10 kilograms of water by 8 degrees Celsius, how much energy do you need to add to the water? So as usual, I'll just write down what I know. I know the specific heat, the mass, and the change in temperature. So just plugging that into the equation gets me 334,880 joules. That seems like a lot, but we're going to be dealing with very high amounts of energy in this unit in general. It takes a lot of energy to change the temperature of even simple materials by just a little bit. In example number 2, we're using water again, but this time we're taking away 200,000 joules from 4 kilograms of water, and we want to know how much the temperature will change by. Because we're taking heat energy out, this is going to cool the water. It's going to decrease the temperature. So just writing out what I know the specific heat, I know the mass, and I know the change in energy. That's negative 200,000 joules. So solving for the change in temperature, I can just plug this into Q equals mc delta T, and solving for the temperature on its own gets me a final answer of negative 11.9 degrees Celsius. In problem 3, again, we're using water. What is the mass of water that would gain 30 degrees Celsius if you added 10,000 joules of internal energy? So remember, internal energy is the same thing as thermal energy, and adding that is the same thing as heat. It's the change in thermal energy. So again, I'll just write down what I know. And we're trying to solve for mass. Plugging that into the equation and isolating mass gets me a final answer of 0.08 kilograms. Finally, in example problem 4, 30 degrees of iron is heated by 3 Kelvin when 40,500 joules of energy is added to it. What is the specific heat of iron? So I have the mass, I have the change in temperature, and remember this equation works whether we're using Kelvin or Celsius because the changes in temperature are the same on both scales. And the energy is 40,500, that's the heat added. And we're trying to find the specific heat. So again, I'm just using Q equals mc delta T, plugging in my numbers and isolating C gets me a final answer of 450 joules per kilogram Kelvin. Just a quick note, the specific heat equation only applies when the material is changing temperature. There are specific temperatures where the material changes its state, like when it changes from a solid to a liquid when it's melting. And when this happens, energy goes into changing the state or the phase of the material instead of the temperature. This means that we cannot use Q equals mc delta T by itself when a material crosses a temperature that causes it to change its state. That's going to be the theme of the next few videos, but for now you just need to remember that you can only use this equation when the material is changing its temperature. When it's changing its state, when it's melting or freezing or evaporating or condensing, we're going to use a different equation that we'll learn about in the next few videos. This lecture is about latent heat. Latent heat is a measurement of how much energy it will take to change 1 kilogram of material from one phase to another when the material is at the correct temperature to change its phase. Latent heat is equal to the heat required to change the phase divided by the mass of the material you're trying to change. This equation is more often written as Q equals M times L. Each material actually has 3 latent heats: fusion, vaporization, and sublimation. The latent heat of fusion is the amount of energy per kilogram consumed when changing from solid to liquid, or the amount of energy released per kilogram when changing from liquid to solid. The latent heat of vaporization tells you about going from liquid to gas or gas to liquid, and the latent heat of sublimation tells you about going from solid to gas or gas back to solid. Just as an example, these are the latent heats of fusion and vaporization for water. The latent heat of fusion is 3.3 times 10 to the 5th joules per kilogram, and the latent heat of vaporization is 2.3 times 10 to the 6th joules per kilogram. So if we imagine that we have 1 kilogram of ice here on the left, and we want to change it entirely to water, that latent heat of fusion is telling me that I need exactly 3.3 times 10 to the 5th joules to completely melt the ice to water, assuming that the ice is at its melting point. So if the ice is at its melting point of 0 degrees Celsius, and I add this amount of energy to the ice, that's going to convert all of the ice into water. So that's what the latent heat of fusion is physically telling me. The latent heat of vaporization is telling me that if I want to convert 1 kilogram of water into steam, and the water is at its vaporization point, if I have exactly 1 kilogram of water, I need to add exactly 2.3 times 10 to the 6th joules to completely convert the water into steam. The latent heat also tells me how much energy I would need to remove to change the phase in the opposite direction. So if I had 1 kilogram of water and I wanted to convert it back to ice, and it was at its freezing point, I would need to take out 3.3 times 10 to the 5th joules from the water to convert it back to ice. And if I had steam at its vaporization point, and I wanted to convert it back to water, I would need to remove 2.3 times 10 to the 6th joules of heat from the steam. Because the latent heat is measured per kilogram, if I have 2 kilograms instead of 1, I would need 2 times the latent heat in energy to convert that doubled mass all into water. And for vaporization, again, because the latent heat is 2.3 times 10 to the 6th joules per kilogram, if you have 2 kilograms, you would need 4.6 times 10 to the 6th joules to convert that water into steam. And obviously going backwards works the same way. We can now do a few example problems before moving into another important concept about latent heat. Example problem 1 says how much energy would it take for 5 kilograms of ice at 0 degrees Celsius to melt into water at 0 degrees Celsius. I'm going to be using this table on the right with information about water. I can see that I now have the specific heat for all 3 phases of water, the latent heat of fusion and vaporization for water, and the melting point and boiling point for water. So I can see that when the material is ice and when it's water, it's at 0 degrees Celsius, so it's at the correct temperature to change its phase. So I can use the latent heat equation to find the energy used. Because we're going from solid to liquid, we're going to use the latent heat of fusion, which I can see from the table is 3.3 times 10 to the 5th joules per kilogram. The mass is 5 kilograms, so plugging that into Q equals M times L, I get 1.65 times 10 to the 6th joules. That's how much energy would be required to melt 5 kilograms of ice into 5 kilograms of water at 0 degrees Celsius. Example problem 2 says how much energy will be released from 20 kilograms of steam at 100 degrees Celsius if it completely condenses into water at 100 degrees Celsius. So the temperature is already at its boiling point, so that means that it's ready to change its phase. So we can use the latent heat equation. And we're going from gas to liquid, so this time we're going to use the latent heat of vaporization. So that's 2.3 times 10 to the 6th joules per kilogram. The mass is 20 kilograms, and I'm trying to find the energy. Plugging that into my equation gets me 4.6 times 10 to the 7th joules. That's how much energy would need to be removed from the steam to turn it back into water. So now that we know about both the latent heat and the specific heat, we can now use the equation for specific heat and latent heat to find the total energy required to change the temperature and phase of a mass of material. So just to show you what's happening here, I'm going to return to this animation where I'm adding a constant amount of heat to a material, in this case a solid that starts at absolute 0. So as I add this energy, I want to know how much energy I'm adding in total, or maybe I want to know how much the temperature is changing, or how much energy will be required to change the phase or the mass of the material. As I try to understand different parts of this material's change, I need to remember that as I start to add energy in, if the material isn't at a temperature where it changes its phase, all of that heat energy is going into changing its kinetic energy. So in the beginning here, I could only use Q equals mc delta T to understand how much energy I'm adding or how much the temperature is changing. So that equation applies for any temperature outside of the temperatures where a material changes its phase. When it begins to change its phase, all the energy suddenly goes into changing the phase instead of the temperature, and we have to use this equation instead, Q equals ml, to understand the phase change. So this equation applies as long as the material is changing its phase, so now all the heat is going into changing its phase from solid to liquid. So this equation can tell me exactly how much energy was required to do that. Once it's done changing from a solid to a liquid, I'm now in the position where the only equation that applies is Q equals mc delta T, and that will continue to be true as long as this is adding kinetic energy to the material until its temperature hits the boiling point. And when it does that, the energy is no longer changing its temperature, it goes back to going into changing its phase, and I can use Q equals ml to understand what's happening, and the total energy that's going into changing the material from a liquid into a gas. And once the phase is completely changed and it's a gas, all the energy goes back into changing its temperature, and Q equals mc delta T applies for the rest of the problem. So that was a visual of what's going on here. I'm now going to give you a few more complicated example problems where we combine both of those equations. Example problem 3 says you have 2 kilograms of water at 20 degrees Celsius, and you want to heat it until the moment it is completely evaporated into gas. How much heat do you need to supply? So the water needs to be heated from 20 degrees to its boiling point at 100 degrees Celsius. That's where it begins to convert into gas. And then its phase needs to be changed from liquid to gas. So I'm going to split this up into two problems. I'm going to start by finding the heat required to reach that boiling point of 100 degrees. And then I'm going to find the heat required to evaporate the water once it's at 100 degrees Celsius. So to find the heat required when you're changing temperature, I know that the mass is 2 kilograms. The change in temperature is going to be 80 degrees because we're going from 20 to 100. And I need the specific heat because we're changing temperature. And my table says that the specific heat of water is 4.2 times 10 to the third joules per kilogram degree Celsius. So plugging that into my equation gets me 672,000 joules of energy required to heat the water from 20 degrees Celsius to 100 degrees Celsius. At the moment that we've heated it to 100 degrees Celsius, it still exists as water, so we now need to add heat to change its phase instead of its temperature. So the heat required to change its phase is going to be its mass of 2 times the latent heat of vaporization, because that tells us about going from liquid to gas or gas to liquid, and from my table I can see that that's 2.3 times 10 to the 6th joules per kilogram. So I can plug that into my equation Q equals ml and solve for the heat. So we can see that's 4,600,000 joules. So the total additional energy, the total heat required, is going to be the sum of those two, because we need to first get it to 100 degrees and then completely evaporate it. So adding those together gets me a final answer of 5,272,000 joules. So that is exactly how much energy you need to add to 2 kilograms of water to heat it from 20 degrees Celsius to 100 degrees Celsius and then completely evaporate it. In example problem number 4, you want to heat 5 kilograms of negative 15 degrees Celsius ice until it becomes 20 degrees Celsius water. How much heat do you need to supply? There are 3 steps we need to take here, because the water needs to be heated from negative 15 degrees to its melting point at 0, and then its phase needs to be changed from solid to liquid, and then its temperature needs to be raised from 0 degrees Celsius to 20 degrees Celsius. So we need to split this into 3 problems and find the heat required for each individual step. To find the heat required to reach its melting point, I know its mass is 5 kilograms. The change in temperature is 15 because we're going from negative 15 up to 0. The specific heat of ice is 2.1 times 10 to the third joules per kilogram degree Celsius. I got that from my table. And so the heat is going to be equal to 157,500 joules. To find the heat required to melt the ice, I know the mass is 5, and because we're going from solid to liquid, we use the latent heat of fusion, which is 3.3 times 10 to the 5th joules per kilogram. Plugging that into ml gets me 1,650,000 joules required to melt the ice into water. And then to heat that newly melted water up to 20 degrees Celsius, I have a mass of 5, change in temperature of 20, and the specific heat of water is 4.2 times 10 to the third joules per kilogram degree Celsius. So the total heat required is going to be 420,000 joules. So altogether, those 3 heats put together, the total heat required to increase the water's temperature from negative 15 degrees to positive 20 degrees is going to be 2,227,500 joules of energy. This is the last problem. What mass of water would heat from negative 30 degrees Celsius to 120 degrees Celsius if 2 million joules of heat were added to it? Okay, this is a very long problem because we first need to heat the water until it reaches its melting point, and then melt the water, and then heat it to its boiling point, and then boil it, and then cause it to reach 120 degrees Celsius, because that temperature change goes over both the melting temperature and the boiling temperature. So I'm not going to talk through this, I'm just going to show you all the individual work that would be required to find the heat for each one, and because I'm trying to find the mass, I'm keeping that as a variable in each equation for heat. So once I have the energy required to take each one of these steps, I can say that altogether that energy is equal to this total energy, that mass multiplied by 3,153,000 joules per kilogram. And I know that altogether that's equal to the energy that we're adding of 2 million joules. So solving for the mass there gets me a final mass of 0.63 kilograms. So that's exactly how much mass would be heated by exactly that much if we applied that much thermal energy to it. So even for very complicated problems like this, all you really have to do is break it down into steps where you're either changing the temperature when it's not at its melting or boiling point, or changing its phase when it is at its melting or boiling point. And that applies to any substance, not just water. This can still be an overwhelming amount of numbers, so in a future lecture, I'm going to show you how to construct a temperature versus heat graph to do these same calculations, but with a much easier way of displaying them. This lecture is going to be about how to use power and heat equations. Because power is a change in energy over time, and heat is a change in energy, we can rewrite the power equation for this unit as power is equal to heat over time. This allows us to connect what we know about heat to time so we can determine how long it will take to heat and cool materials. Rearranging that equation gets me time equals heat over power. As an example, we could say a constant power supply of 5,000 watts is used to heat a 10 kilogram block of ice at its melting point. Using the table of information for water, determine how long it will take to completely melt the ice. Because this is changing phase, we're going to use Q equals m times L, and I know that the power is 5,000 watts, the mass is 10 kilograms, the latent heat of fusion for water is 3.3 times 10 to the 5th joules per kilogram, and we're using fusion because we're going from solid to liquid, and we're trying to find the time. So I know that power is equal to heat divided by time, so that means that time is equal to heat divided by power, and I can rewrite that equation replacing Q with m times L. So now I have what I'm looking for, T, and everything I have, m and L and P. So I can just plug those into my equation and find that it would take 660 seconds for a power supply of 5,000 watts to completely melt 10 kilograms of ice at its melting point into water. Example number 2 is asking how much power would be required to heat 20 kilograms of water from 10 degrees Celsius to 30 degrees Celsius in 5 minutes. So this is a change in temperature, so we're going to use Q equals mc delta T. I know that the mass is 20 kilograms, the change in temperature is positive 20 degrees Celsius, the specific heat of water is 4.2 times 10 to the 3rd joules per kilogram degree Celsius, and the time is 5 minutes, which I can show is equal to 300 seconds. So the power is equal to the heat over the time, replacing heat with mc delta T, and plugging those numbers in, gets me 5,600 watts of power to change the temperature of 20 kilograms of water by 20 degrees Celsius. In example number 3, a stove provides 2,000 watts to 10 kilograms of water initially at 20 degrees Celsius. How much time would it take to completely evaporate the water? The water is changing temperature and then phase, so we need to use Q equals mc delta T and then Q equals ml. I'll start by solving for the time it takes the water to reach its boiling point. The mass is 10 kilograms, and we're trying to get it up to 100 degrees Celsius. That's the boiling point of water according to my table on the right. So that means the change in temperature is positive 80 degrees Celsius. And the specific heat of water is 4.2 times 10 to the 3rd joules per kilogram degree Celsius. And the power is 2,000 watts. So plugging this into my equation, knowing that Q is equal to mc delta T, gets me a time to reach the boiling point of 1,680 seconds. Now I need to find the time required for the water to change its phase. The mass is 10 kilograms. I know that we're working with the latent heat of vaporization because we're going from liquid to gas. So that's going to be 2.3 times 10 to the 6th joules per kilogram. The power is 2,000 watts. So again, plugging this in, knowing that Q is equal to m times the latent heat of vaporization. Plugging that in gets me 11,500 seconds. So the total time is going to be 1,680 seconds plus 11,500 seconds, which is equal to 13,180 seconds. So those are 3 examples of how you can use the power equation to calculate power and time when you're working with heat. This video is about how to read, draw, and do calculations with a temperature versus heat graph, or a temperature versus time graph. This is what a temperature versus heat graph looks like. You can see it has temperature measured in Celsius on the y-axis, that could also be Kelvin, and heat measured in joules on the x-axis. I've added a thermometer on the left just to give you an intuition of how the temperature is increasing over time. The goal of using graphs in physics is to represent a lot of information that would be really painful to write out in words using pictures that are as simple as possible. We use temperature versus heat graphs to understand how the temperature of a material changes as we add heat, And we can find patterns in the graph that can tell us about the specific heats of the solid, liquid, and gas form of the material, and the latent heat of fusion and vaporization of the material, in addition to a lot of other information. So we're going to make a temperature versus energy graph for 1 kilogram of water that starts at negative 100 degrees Celsius and ends at positive 200 degrees Celsius. You can see I have a box with information about water, its specific heat as ice, water, and steam, and its latent heat of fusion and vaporization. I also have a box on the top right that's going to display what state of matter the water is in at each point along the graph. You can see I also have the two heat equations that we use when doing these types of calculations. When temperature is changing, we're going to use Q equals mc delta T, and when phase is changing, we're going to use Q equals m times L. I'm going to start by labeling important temperatures on the y-axis of the graph. First of all, I know that this water is starting off at negative 100 degrees Celsius. So in the top right, I know that its state of matter is going to begin as a solid. And I've lined that number up with this imaginary thermometer so you can get an intuition about how the temperature is changing. I know that 0 degrees Celsius is the melting point of water, and the boiling point of water is 100 degrees Celsius. And the final temperature this water is going to reach is 200 degrees Celsius. I tried to space those out evenly so they represent equal increments. So this is the full range of my graph. This is where it's going to appear. So I'll begin to fill out any information that I know about this water. I know first of all that it's starting at a temperature of negative 100 degrees Celsius, so that's where the first point will be. And as we move to the right along the graph, the x-axis means that more and more heat is being added. So as heat is added to this water, I know that it won't be changing its phase because it's not at its melting point yet. And when temperature is changing, we can use Q equals mc delta T to understand the relationship between the heat and the temperature. I can see that the change in temperature is 100 degrees Celsius. That's how much the water is going to heat before it does something different, before it reaches its melting point, and I have to use a different equation. I also know that its mass is 1 kilogram, and the specific heat of water is 2.1 times 10 to the third joules per kilogram degrees Celsius. So if I bring all this information into my equation, I can use that to figure out exactly how much heat is going to be added over that increase of 100 degrees Celsius. When I do that calculation, I get 210,000 joules. So that means that as the temperature increases by 100 degrees Celsius, the water gains 210,000 joules. So I'll mark off a little point on my graph right there to mean that 210,000 joules have been added. Because you can see that neither T or Q are squared in this equation, and the mass and the specific heat stay constant, Q and delta T have a linear relationship with each other, so these graphs are always going to be linear. They'll always be straight lines like this if we're working in ideal situations. So I know that this graph would start at negative 100 degrees Celsius and increase linearly until it's 0 degrees Celsius. It's at 210,000 joules of heat energy. So this gives me a visual of how much heat energy I need to add to increase its temperature by 100 degrees. And I know that over that time, the water is in its solid state. When the water hits 0 degrees Celsius and continues to receive heat, it stops changing its temperature because it's at its melting point where it begins to change its phase instead. So it's going through the phase change fusion, which we know better as melting. When material is changing phase, we use Q equals mL to understand the relationship between the heat and the mass. And I can see that the latent heat of fusion for water is 3.3 times 10 to the fifth. So the total heat energy required for the full phase change is 330,000 joules. Because we're already at 210,000 joules, adding an additional 330,000 gets me to 540,000 joules. And during a phase change, the temperature does not change. All of the heat goes into changing the potential energy in the particles rather than the kinetic energy. So that means that the temperature remains constant as it changes its phase. Once the water is completely done changing its phase, it exists entirely as a liquid, and heat added goes back into changing the temperature. So we can now use that first equation to understand how much additional heat will have to be added to increase the temperature to 100 degrees Celsius, where the water begins to boil. So using Q equals mc delta T, I can see that my new change in temperature is going to be 100 degrees Celsius. So when I bring that information down, and I know that the specific heat of water is 4.2 times 10 to the third joules per kilogram degree Celsius, I can use that to find how much heat will be required to heat the water in additional 100 degrees Celsius. That turns out to be 420,000 joules. So altogether, that will be at a point of 960,000 joules. So this line represents how the temperature will increase over time. So this line represents the state of the water when it's in its liquid phase. The advantage of drawing these graphs is that I could look at any one point along that line and understand exactly how much energy the water had for any one point. If I wanted to know exactly how much heat had been added when the water was at 50 degrees Celsius or 70 degrees Celsius, I could also use this graph to figure that out. When the water hits 100 degrees Celsius, the additional heat goes into changing its phase because now it's at its vaporization point. So when phase is changing, we use Q equals mL, and here L is the latent heat of vaporization, which is a very big number. Plugging that in gets me 2,300,000 joules, which is much bigger than the other numbers we've used so far, as you can see here. Adding that number to what I already had gets me a final number of 3,260,000 joules. And all through that time, while that heat is being added, the water is going through a phase change, so the temperature is not changing at all. So this line represents the water going through vaporization. Finally, the water is going to exist as a gas once it's been completely vaporized. And now that you know that, I'm actually going to get rid of the state of matter box just so I have a little more room. So in this last section of the graph, we're going from 100 degrees to 200 degrees Celsius. And because we're not changing phase anymore, we're changing temperature. So we're using Q equals mc delta T. I can see that the change in temperature will be 100 degrees Celsius to get us up to 200 degrees Celsius. Plugging that in, along with the specific heat of steam, gets me 200,000 joules of heat added to the water. That's how much heat will be required to get it up to 200 degrees Celsius. Altogether, I've now added 3,460,000 joules of heat energy to this water, and the water has now achieved 200 degrees Celsius, and it was a gas over that time. The reason why we like these graphs so much is that they can be used to find the energy required to heat a material from any temperature and phase to any temperature and phase. As an example, if we wanted to know how much energy it will require to completely evaporate ice that is frozen at 0 degrees Celsius, if ice is frozen, it's completely in its solid state. So if it's a solid at 0 degrees, the graph would have to start right here, right before it undergoes fusion. And the exact moment that it's completely evaporated will happen when vaporization is complete. So if I trace out how far it is from that point where it's a solid at 0 degrees Celsius to the point where it's completely vaporized, I can see that the total energy added will be that final energy minus the energy that it started with. So the energy required to completely evaporate ice frozen at 0 degrees Celsius, if there is just 1 kilogram of that ice, is 3,050,000 joules. We can rearrange Q equals mc delta T to fit y equals mx plus b so we can understand something about the slope. Q is the x value and delta T is the y value, so if I rearrange it, I get delta T is equal to 1 over m times c, all multiplied by Q. And if I match that up with y equals mx plus b, I can see that 1 over mc is equal to the slope. It's equal to the m value in mx plus b. So that means that the slope of this graph is always equal to 1 over the mass times the specific heat. And notice that because mass stays constant, a larger specific heat will mean a smaller slope. So if the line is steeper, that actually means you have a smaller specific heat. We can also observe how the potential and kinetic energy changes as energy is added over time. Just remember that changing temperature means the particles are gaining or losing kinetic energy, and changing phase means the particles are gaining or losing potential energy. So in every section where the water is gaining temperature, kinetic energy is being added, and wherever it's changing phase, potential energy is being added. So these are the places where kinetic and potential energy are being added respectively. So the energy that exists between each gap there is either going into kinetic energy or potential energy in the particles of the material. I can now trace through this entire graph and make a very detailed animation of what's happening to the temperature of the material, the state of the matter, the movement of the particles in the material, because remember, if you add internal kinetic energy, the particles begin to move faster. I can also show the bonds between the particles. And on the right, I'm going to graph the exact value of the energy of potential and kinetic energy as we go along the graph. So if we start at negative 100 degrees Celsius, the potential energy is very low because we're going to have to add that exact amount of potential energy to convert the material to water and then to steam. And like I said in a previous lecture, potential energy in the bonds of particles is recorded as negative. The water does have some kinetic energy already, just because it's not at absolute zero. If you compared its energy from absolute 0 to negative 100, you'd find that it's 3.6 times 10 to the 5th joules, so that's what I've recorded on the table on the right. So I'm just going to have you sit back and watch and observe what's happening to each value and each quality of the material as we trace along the graph. So the kinetic energy is increasing, the temperature is increasing, it's a solid, the movement of the particles is getting bigger. And then here the state of matter is changing, and so the potential energy is increasing, and the bonds between the particles are getting less strong. Then here, more kinetic energy is being added, the temperature is increasing, the state of matter is constant as a liquid, and the particles are moving faster and faster. They're gaining more motion, and the bonds of the particles are remaining the same because the phase isn't changing. Then when we get to 100 degrees Celsius, The potential energy is increasing, it's going through vaporization. The temperature and kinetic energy and movement of the particles are all not changing. Finally, when all the negative potential has been removed, there are no bonds between the particles anymore, and the water now exists as gas, as steam. Finally, the energy added goes into kinetic energy, which increases the temperature of the water and the movement of the particles, and the water remains as steam. I'm going to play that one more time without narration just to make sure you're taking in all the information. Any temperature versus heat graph can also be drawn as a temperature versus time graph if we assume a constant rate of power is being supplied to heat the material. As an example, we can imagine that we have a constant power supply of 100,000 watts, and we can ask how much time does it take to heat the water from negative 100 degrees Celsius to positive 200 degrees Celsius. Because power is heat over time, time is equal to heat over power. So for each value of heat I have on my x-axis, I can replace that with a value of time by just plugging it into time is equal to heat over power. This first number means that if you want to get to 210,000 joules and you're supplying 100,000 watts of power, it's going to take 2.1 seconds to supply that much heat. So that means that it takes 2.1 seconds for the water to hit its fusion state. It takes 5.4 seconds to reach this state, 9.6 seconds to reach this state, 32.6 seconds to reach this state, and 34.6 seconds to reach this state. So we no longer have a heat graph here, we have a temperature versus time graph. So temperature versus time graphs assume a constant rate of power being supplied. Now that we've built a temperature versus heat graph, I'm going to move into some general information that's true for any temperature versus heat graph. The phase changes obviously always appear at the temperatures of the melting point and the boiling point. The energy changes between each phase and in each phase are written on the x-axis. So each interval of energy is equal to that exact value. Just as a note, the x-axis can be read forward or backward. If we trace the graph backward, it means we are taking heat out of the material, so the material would experience condensation and freezing instead of fusion and vaporization. The amount of energy involved in a phase change is the same no matter which direction you're changing the phase. It's just that if you're moving to the left along the graph, that means that you're reducing the energy involved. So condensation reduces the energy by the same amount that vaporization increases it by. If we assume a constant power supply, we can rewrite those equations on the bottom as their heat equations divided by the power being supplied. That can tell us the time it takes to complete each process on the graph. The solid region is the point where the particles have the least kinetic and the least potential energy. With liquid, they have more kinetic and more potential, and in gas, they have the most kinetic and most potential. And just a reminder that potential in a gas is 0. The reason why that's the most is that the other phases have negative potential. We can compare different points along the phase changes and ask what's happening at each one. Right at the point where the material is in its solid phase, but it's hitting its melting point, is where it's still completely a solid, but it's in its melting point. It's ready to be melted. At the halfway point between them, some of the material is solid and some of it is liquid, so it's not quite done with the phase change in either direction. And at the other end of the fusion freezing line, the material is still at its melting point, but is now completely a liquid. And you can see there's a similar pattern when it's vaporizing or condensing. I'm going to give you a few examples of sections of the graph that correspond to specific descriptions. We could imagine that you're asked to describe the material that starts at a temperature A below the melting point, and heat is added to it until the exact moment it has completely evaporated. So on the graph, that would look like this. There's some temperature A below the melting point, and this is the exact moment where it stops evaporating. So this section of the graph would be what the question is asking about. So you could find specific properties of the material over that time. For example, you could use the x-axis of the graph to find the total heat added, the total heat required to get from temperature A to the point where it's completely evaporated. In comparison, if we drew a line from temperature A to the exact point where the material begins to evaporate, it begins to evaporate here, right when the liquid reaches its boiling point, so this would involve a lot less energy than the other description. So this would be the total heat added there. We could say that the material starts at temperature A above the boiling point and emits heat, it's losing heat, until it's at temperature B between the melting and boiling point. So this could be where A is, this could be where B is. It would start here and there, and we could use this line to understand how much energy was physically lost. We could say the material begins as gas at its boiling point and emits heat until the exact moment it is completely solid. So this would be where the gas at its boiling point is, and the exact moment it becomes completely solid is right here at the end of its freezing state. So this would be the line we would draw. and this would be how much heat was lost. If you're given numbers on the axes of a temperature versus heat graph and asked to find the specific heat and latent heat of the material, you can use the fact that the horizontal length of a line on a graph is equal to the heat added and the vertical length is equal to the temperature change. As an example, we can imagine that the mass of the object being graphed is 2 kilograms, and we want to know what is the material's latent heat of fusion and what is the material's specific heat in its liquid phase. I'll start by finding the latent heat of fusion. I know that that only applies in the fusion or freezing phase change, so I'm only going to pay attention to that. I can see that that phase change requires a total of 6 joules of energy according to the x-axis, and the mass is 2, and we're trying to find the latent heat of fusion. So I know that this equation applies because it's a phase change. Isolating the latent heat of fusion gets me an answer of 3 joules per kilogram. So that would be the object's latent heat of fusion. And so we can get that just based off of the x-axis of the graph. Question B asks, what is the material's specific heat in its liquid form? So to understand specific heat, that only applies when temperature is changing. So I'm just going to look at the line where the temperature is changing and it's a liquid. Drawing that out, I can see that the change in heat is 7 joules. 7 joules are added from 8 to 15. The mass is 2 kilograms. The change in temperature is 40. It goes from 20 degrees to 60 degrees. And we're trying to find the specific heat. Plugging that into MC delta T gets me 0.088 joules per kilogram degrees Celsius. So that would be the specific heat. So again, we can find that just by using the graph to know the change in temperature on the y-axis and the heat on the x-axis. That's all the information that you need to know about how to read temperature versus heat graphs. This lecture is about thermal equilibrium. Thermal equilibrium itself is a very simple idea. Two objects are in thermal equilibrium if they have the same temperature. That's all that the word itself means. So these two objects here are both at 20 degrees, so they're at thermal equilibrium, and these two objects are not in thermal equilibrium because they're not at the same temperature. The definition itself is extremely simple. There's a rule that scientists call the zeroth law of thermodynamics that says if A and B are in thermal equilibrium, and B and C are in thermal equilibrium, A and C are also in thermal equilibrium. And if you think about that, that's an incredibly simple intuitive law, because all that that's saying is that if A has the same temperature as B and B has the same temperature as C, A also has the same temperature as C. Two objects are in thermal contact if heat can move between them. Thermal contact usually just means two objects physically touch. So I can see that these two objects are not in thermal contact with each other because there's an insulating barrier between them, some barrier that insulates heat and prevents the heat from moving through it. And these two objects are in thermal contact because they're making physical contact and heat is moving from one object to the other. Those definitions were very simple. This rule that I'm introducing now is the challenging part of the concept and where the math comes into it. When two objects are in thermal contact, heat will move from the higher temperature to the lower temperature object until the two objects are in thermal equilibrium. Once they reach thermal equilibrium, heat stops moving between them. This rule is true whenever any two objects in the universe enter into thermal contact with each other. When they do, heat begins to move from the higher temperature to the lower temperature object until they have the same temperature. So here I have two objects at different temperatures, as you can see by the thermometers I put next to each one, and I also have a graph of their internal energy below each object. I'm going to move these two objects into thermal contact and observe what this rule tells me about what will happen. So when they enter into thermal contact, heat begins to move from the higher temperature to the lower temperature object, so it will move out of the blue object and into the green object. It will continue to do this until the two temperatures are equal. So the heat moving through specifically means that internal energy is moving from the blue object to the green object. The green object's temperature rises and the blue object's temperature falls. And this continues until the two temperatures are exactly equal. So this is the point where they're exactly equal. And now that they're in thermal equilibrium, heat will stop moving from one object to the other. So when they reach thermal equilibrium, heat stops flowing. You'll notice that the internal energy does not have to be equal because internal energy is different from temperature. But what does have to be equal here is the change in energy, the heat, from one object to the other. The heat lost by the higher temperature object must always equal the heat gained by the lower temperature object. So just to repeat, when two objects are placed in thermal contact, heat flows from the higher temperature to the lower temperature object until both objects are in thermal equilibrium, until they have the same temperature. And as that happens, any heat lost by the higher temperature object is gained by the lower temperature object. Because energy is conserved and has to go somewhere, it can't just be created or destroyed. So the final temperatures of the two objects in thermal contact are equal, and the heat lost by the hotter object is equal to the heat gained by the colder object. So these are always true in thermal equilibrium problems. The final temperature of the two objects will always be equal, and the heat lost by one will be equal to the heat gained by the other. And again, notice that the internal energy of the two objects does not have to be equal, but the temperature does. These two facts are enough information to solve for missing information when two materials are placed in thermal contact and allowed to reach thermal equilibrium. There are two types of thermal equilibrium problems we can talk about. Problems where only the temperature changes. These are easier, and we only need to use Q equals mc delta T for those. But there are also problems where we place objects in thermal contact and both the temperature and the phase changes. These are harder, and we would have to use both Q equals mc delta T and Q equals ml for when the phase is changing. So I'm going to give you a few examples of both. This is the first example. We're only dealing with temperature change here. A 2 kilogram piece of metal with a specific heat of 1000 joules per kilogram degree Celsius is at a temperature of 20 degrees Celsius. A 3 kilogram piece of metal with a specific heat of 1500 joules per kilogram degree Celsius is at a temperature of 80 degrees Celsius. When they are placed in thermal contact, what final temperature will they reach? So I need to use what I know about Q equals mc delta T, and also this new information about thermal equilibrium, where the energy lost from one is gained by the other, and the final temperatures are the same. I'll start by writing down everything I know. This is the information for metal 1, and we're trying to find the final temperature of metal 1. I can connect these using Q equals mc delta T, and this is what that looks like when I plug numbers into that equation. Just one note, I've replaced delta T by T final minus T initial because those two things mean the same thing. The change in temperature is equal to the final temperature minus the initial temperature. Now for metal number 2, this is the information that I have about it. I can plug this information into Q equals mc delta T, and this is what I get here. I know that the change in energy, the heat in metal 1, will be equal to the negative change in metal 2, so Q1 equals negative Q2. So I can plug in my two equations for Q from metal 1 and metal 2 and set them equal to each other. I know that because the two metals are reaching thermal equilibrium, that means that their final temperatures are the same. So I now have an equation with only one missing variable. I'm only missing T final because the T final on both sides is the same T final. So that means that I can just use algebra to isolate T final by itself. And I'm going to assume that at this point you can do that algebra to isolate T final in that equation. When I do that, I find that the final temperature is equal to 62 degrees Celsius. So this is pretty interesting. I can now use what I know about thermal equilibrium to calculate the exact final temperature of any two objects of different mass, different specific heats, and different temperatures that are placed in contact with each other. Example 2 says a 0.03 kilogram piece of metal is heated in a Bunsen burner, and after it is dropped into 0.04 kilograms of 280 Kelvin water. The metal heats the water until the water is at 348 Kelvin. If the specific heat of the metal is 1230 joules per kilogram Kelvin, and the specific heat of water is 4180 joules per kilogram Kelvin, what is the temperature of the Bunsen burner flame? I'll write down variables for the metal and for the water. So the metal has a mass of 0.3 kilograms, I have its specific heat, I have its final temperature, and I know that the final temperature of the metal is 348 Kelvin because it's reaching thermal equilibrium with the water. That's when it stops heating the water. So by the rule of thermal equilibrium, if the metal stops heating the water at 348 Kelvin, the metal must also be at that same temperature for heat to stop flowing. So I know that the final temperature of the metal is 348 Kelvin. And I want to know the initial temperature of the metal because that starting temperature that it had would be the temperature of the Bunsen burner flame that it was taken out of. Because the flame was being used to heat the metal until the metal reached thermal equilibrium with the flame, and the metal was then taken out and placed in the water. So the temperature that the metal starts off with in the water will be equal to the temperature of the flame it was in before being placed in the water. Again, I know Q equals mc delta T. I'll rewrite this with my specific variables, but I'm going to hold off on plugging in actual numbers until a little later. I'll now write down what I know about the water. So this is the mass of the water, its specific heat, its final temperature, and its initial temperature. So I actually have all the variables I need to use Q equals mc delta T here. So if I plug this in, I get the heat added to the water is equal to 11,400 joules. And I know that because this is a thermal equilibrium problem, because the metal is exchanging heat with the water, the amount of heat added to the water is equal to the amount of heat lost from the metal. So that means that Q metal is also equal to 11,400 joules, just negative instead of positive. I can now plug that into my equation and solve for the initial temperature of the metal. Now I just use algebra to isolate the initial temperature of the metal, and I get an initial temperature of 3,790 Kelvin. In example 3, an object of mass M1 has a specific heat C1 and an initial temperature of 40 Kelvin. A second object of mass M2 has an initial heat of 110 Kelvin. After they are placed in thermal contact, they reach a temperature of 55 Kelvin. In terms of M1, M2, C1, and the temperatures given, what is the specific heat of the second object? So this is the information I have about object 1. I can see that the change in temperature is positive 15 Kelvin. Plugging that into Q equals mc delta T gets me this. Object 2, this is the information I have about it, so I can see that that change in temperature is negative 55 Kelvin. So this is the information I have when I plug that into Q equals mc delta T. And I can connect those two equations using the fact that their two heats are equal to each other, just one is negative. So when I plug in my values, I get this. And the question is just asking for the specific heat of the second object in terms of the other variables. So if I get C2 by itself, this is what that final equation looks like. 0.27 M1, M2 to the power of negative 1 times C1. So that would be the equation for the specific heat of the second object. I'll now do one example where both temperature and phase changes. These are definitely harder. 1 kilogram of ice at its melting point, 0 degrees Celsius, is added to 10 kilograms of water at 90 degrees Celsius. What is the final temperature of the water after the ice melts? The specific heat of water is 4,186 joules per kilogram degree Celsius, and the latent heat of fusion of water is 334,000 joules per kilogram. Okay, so I'll write down everything that I know. We've got ice, we've got water. This is the mass of the ice, initial temperature of the ice. We need the final temperature of the ice, that's the goal. The latent heat of fusion of the ice. We're dealing with a phase change and a temperature change, so to understand the total amount of energy required, the total heat required, we'll need to use both Q equals mL and Q equals mc delta T. So the total heat added to this ice is going to be the heat required to change its phase, m times L, plus the heat required to change its temperature, mc delta T. So you can see I've written both into that equation. One plus the other will be the total heat added to the ice to change its phase, ml, and then its temperature, mc delta T. The water has a mass of 10. The initial temperature of the water is 90 degrees Celsius, and we're trying to find the final temperature of the water. And this is a temperature change, so we just need to use Q equals mc delta T. So this is what I get for the heat taken out of the water, because the water has a higher temperature compared to the ice, so the heat is moving from the water to the ice. I know that the final temperature of the ice will be equal to the final temperature of the water. This is a little confusing just because the ice will be water when it reaches that same temperature. It's going to completely melt. But I'm just going to refer to that mass that's being heated as the ice, even though it's going to become water. I also know that the heat added to the ice will be equal to the heat taken out of the water. So I can set those two equations equal to each other and plug in my values. And again, I know that the final temperature is the same for both, so I'm just calling that TF in both equations. So you can see that even though this is a very long and complicated equation, there's only one missing variable in it. There's only TF. It appears on both sides, but it's only one variable. And the rule is that if we're only missing one variable in an equation like this, we can always solve for that one variable using algebra. So doing the math to isolate T final by itself gets me a final temperature of 74.6 degrees Celsius. So if you take 1 kilogram of ice at 0 degrees Celsius and drop it into 10 kilograms of water at 90 degrees Celsius, and allow the ice to completely melt into the water is going to reach a final temperature of 74.6 degrees Celsius as a result of dropping in that ice. So that's how you do a thermal equilibrium problem when you're dealing with both a temperature and a phase change.
This lecture is going to be a bit different from normal. I'm going to do a video demo with this super awesome simulation of climate change from PhET at the University of Colorado. And then once I've given you a visual of what I'm talking about, I'm going to move back into the normal lecture slides. So to talk about climate change, we need to start by talking about different gases that exist in the atmosphere and an important difference between different types of gases in the atmosphere. So what I have here is a photon gun that's going to fire little photons, little particles of light, at each type of atmospheric gas. So this is a molecule of atmospheric gas. This is specifically CH4, which has the more common name of methane. I'm going to turn this on and notice a pattern in how this molecule reacts to the photons that are impacting it. So you can see photons are coming out, and you'll notice that as the photons go through the molecule, some of the photons just pass right by the molecule, but some of the other photons are absorbed by the molecule and shot off in a random direction. So this is an extremely important pattern. These are infrared photons. That means that they're photons with wavelengths that are too long for us to see. You'll notice that when I shoot visible light at this molecule, nothing happens. So visible light can move through this molecule very easily, but infrared photons cannot. So because visible light can move through, that actually means that this gas is mostly invisible to us, which makes sense because this is one of the gases in the atmosphere, in the air. And because we can't really see the molecules that make up the air, it makes sense that visible light can move through it, but infrared light, light that we can't see, cannot always move through it. Okay, I'm now going to compare methane with an oxygen molecule, O2. So you'll notice that now all the infrared photons are passing right through the oxygen molecule and not being absorbed and bounced out by the molecule. So the infrared photons just keep moving along in whatever direction they already happen to have. I'm now going to go over to a CO2 molecule. You know that better as carbon dioxide. And you'll notice that unlike the oxygen and like the methane, the carbon dioxide molecule is absorbing infrared photons and causing them to bounce off in random direction. It's not doing that for every photon, but for a lot of the photons, it's taking the photons in and then bouncing them back in a different direction. Next on our list of things to test is H2O, which you know better as water. And you'll see here that the water molecule is actually also absorbing and bouncing back infrared photons. So just like methane and carbon dioxide, water is also taking some of that energy in and bouncing it back in a random direction. Last thing to test is nitrogen. Nitrogen is the most common gas in our atmosphere, and you'll see that nitrogen is also allowing photons to just pass right through without bouncing them back in a random direction. So what we've found so far is that methane, carbon dioxide, and water are all types of gases that absorb some infrared photons and bounce them back in random directions, and nitrogen and oxygen do not absorb infrared photons and do not bounce them back in random directions. If I click this button that says Build an Atmosphere, right here I can choose how many of each type of molecule I have present in my atmosphere. So I'm going to make an atmosphere out of just nitrogen and oxygen molecules, and then turn on this little ray. You'll notice that it's now shooting a lot more infrared photons. And the photons are just moving straight through my atmosphere. None of them are being bounced back in any way. However, if I include these other gases like methane or CO2 or H2O, you'll notice that some of them are absorbing the photons and bouncing them back in random directions. And the more of these I include, the more photons get randomly absorbed and bounced back in a random direction. So now that you can see the difference between molecules that absorb infrared photons and molecules that don't, I can give you the formal definition of the difference between those things. So a molecule that absorbs infrared photons we call a greenhouse gas. The reason why we call it a greenhouse gas will be explained in just a moment, but for now you need to know that if it absorbs photons and bounces them back in random directions, it's a greenhouse gas, and if it doesn't absorb photons and just lets them pass right through, it is not a greenhouse gas. So there's a simple reason why we call these things greenhouse gases. It's because when we observe how they behave in the atmosphere as a whole, they behave a lot like glass panes of a greenhouse roof. So greenhouses are glass buildings that are designed to keep plants inside and keep them warm. So if you're trying to grow plants and you don't have a greenhouse, what happens is that visible light from the sun is sent down from the sun to Earth, and the Earth rebounds a lot of that visible light as infrared photons that go back up into space, carrying some energy with them. And if you don't have any kind of layers of your greenhouse to keep your plants safe, all that energy is kind of lost. It just goes straight into space. But if I add a glass layer for this greenhouse, you'll notice that some of the photons get bounced back and stay inside of the area that I've glassed off. And if I add more glass plates, more of those photons are kept from going off into space. So just like those glass layers of an actual greenhouse, greenhouse gases behave in a similar way. What they do is as visible light comes down from the sun and bounces back up, they trap some of the infrared light that's being bounced back up by absorbing them and shooting them off in random direction. So just like we saw over here in the photon absorption simulation, over here, those greenhouse gases are now present everywhere in this atmosphere, and they're going to randomly bounce some infrared photons back towards the Earth. So when I hit play on the simulation, I'm keeping the greenhouse gas levels as they are today, so you'll notice that some of the photons are being bounced back into the atmosphere, while others are leaving back into space, like this. And having some greenhouse gases in the atmosphere is extremely important, because if I set it so that there are no greenhouse gases in this atmosphere, you can see that all of the infrared photons are bouncing back up into space, which means that the Earth is not able to store any heat energy inside of it, and so the temperature plummets way below what we're used to over here. So you can see it dropped very quickly. So some greenhouse gases are definitely very good. And the amount of greenhouse gases in the atmosphere determines how much energy is in the atmosphere. So I'm going to set this up to where the greenhouse gases were at 1750. So you can see that this is how much of each type of greenhouse gas was in the atmosphere in the year 1750. And what's happening here is that some of the energy, some of the photons from the sun are being bounced back into the atmosphere instead of going up into space. And the law of conservation of energy says that energy has to go somewhere. You have to always account for it. So energy is never going to just disappear from the atmosphere or from Earth's system. It has to go somewhere. It can be shot back out into space like some of these red photons up here, or it's going to stay in the atmosphere bouncing around as a photon, which can turn into thermal energy. So the amount of greenhouse gases in the atmosphere determines how much energy the Earth's atmosphere can store at a time, which basically determines the temperature of the Earth. So the greenhouse effect is a really straightforward mechanism. Just because there are a bunch of greenhouse gases in this atmosphere absorbing and shooting off these red photons in random directions, that's keeping some of the energy in the atmosphere of the Earth. So that's causing the Earth's climate to stay at a particular temperature. So you'll notice over here, the CO2 specifically in the atmosphere is 280 parts per million. That means that if you were to take a chunk of the atmosphere, 280 millionths of that atmosphere would be made up of carbon dioxide specifically. And this is in 1750. And the significance of 1750 is that it's a year before the Industrial Revolution, before humans really started to put out large emissions of carbon dioxide to the point where the amount of carbon dioxide in the atmosphere actually changed. So just to give you a demonstration of how much the carbon dioxide has changed and is changing from 1750 to today, and by today it doesn't actually literally mean today, it means when the simulation was created, you can see that after the Industrial Revolution we've jumped up to 388 parts per million of carbon. And it's a little difficult to see, but a few more of these infrared photons are being bounced back and prevented from going into space. And just a little bit more carbon causing a little bit more photons to be bounced back into the atmosphere has just a little effect on the temperature. It can raise it by just a few degrees. So the adjustment from 280 parts per million, where the average temperature is 57 degrees, to today at 388 parts per million when it's about 60 degrees has an effect. What's especially scary about this simulation to me is that this 388 parts per million is already very, very inaccurate just because the simulation is a few years old. The actual amount of carbon in the air as of me recording this video in 2019 is actually 410 parts per million. So just since the simulation was published a few years ago, the total parts per million has already risen from 388 all the way up to 410, which is a pretty huge abrupt shift. And the reason why we're worried about this is that if we continue to increase the amount of greenhouse gases in the air, eventually more and more photons will be trapped by the atmosphere, causing more and more energy to be trapped in the atmosphere, because again, energy cannot be created or destroyed, it always has to go somewhere. This will cause the Earth's temperature to continue to advance up and up and up like this. So this is why climate scientists universally believe that greenhouse gases in particular are the main cause of climate change, and the human addition of more greenhouse gases into the atmosphere is mainly what is changing the climate. What's especially concerning is that the agreed upon dangerous point where global climate change starts to get dangerous is actually at 350 parts per million. So not only were we past that when the simulation was created, but we've also gone significantly far beyond that into 410 parts per million since the simulation was created. So the emission of these greenhouse gases is a main concern in power production. It's probably the main thing that's considered now when new power stations are built, so it's going to be a main focus of this unit as well. Going back into the lecture slides. This is the official definition of greenhouse gases. It's any gas that absorbs and emits radiant energy from the sun. We call these greenhouse gases because they store energy in the Earth's atmosphere like the roof of a greenhouse. And if we significantly change the amount of greenhouse gases in the atmosphere, we will change the energy in the atmosphere, and this causes climate change. And water vapor, carbon dioxide, methane, and nitrous oxide are the 4 most common greenhouse gases in the atmosphere in order of how common they are. And a significant change in the amount of these greenhouse gases is what causes climate change, which is a change in the overall average temperature of a region or of Earth. It's caused by a change in the greenhouse gas makeup of the atmosphere. Some people get a little confused by that definition and assume that it can mean any time weather is changing at all, but it actually means a change in the overall average temperature of the region. So right now, as an example, in Virginia, it drops to a certain temperature in the winter and rises to a certain temperature in the summer, but those by themselves are not examples of climate change. A change in climate would be like if the overall pattern throughout the year of Virginia changed to what the pattern in somewhere like Arizona is like, where the temperatures at specific times of the year are very different from what they are here. So scientists and everyday people and politicians are all very concerned about climate change because it threatens how and where food can be grown and where people can live. And if climate change gets especially bad, it could actually spiral out of control to the point where humans can no longer survive on Earth. There are very different models of what will happen with climate change, and there's no certainty about exactly what will happen, but there's enough of a risk of very extreme bad things happening that people are concerned. And so most of the decisions people make about how to generate power now take climate change into consideration. And so we're going to do that as well in this unit on power. And the IB test also includes questions about climate change along with the rest of the power unit when you're testing on that subject. I'm going to leave a few links in the description if you're interested in looking at this more. The first link I'll put is the link to that PhET simulation I was using at the beginning. I'll also include a video in the description about the specific effects and concerns about climate change. And those effects aren't being tested on in this unit, but they're still very important to know about.
This lecture is about the idea of pressure in physics. Pressure is the force applied per unit area on a surface. The variable is lowercase p, and the unit is Newton per meter squared, or PA, which is short for Pascal, who is a famous mathematician and philosopher who worked a lot with the idea of pressure. The equation for pressure is just force over the area that it's applying on. Pressure is a scalar quantity because information about a material's pressure does not tell you which specific direction force applies. Material with a given pressure always applies a force pointing away from itself. As an example, we can imagine that this green gas is at 10 pascals of pressure and it's contained in this black box where each side has a surface area of 2 meters squared. Because pressure is equal to force over area, the force applied by the pressure is equal to the pressure times the area. So because each side of the box has an area of 2 meters squared, the force on each side of the box is going to be 20 newtons. So the gas in this box is applying an outward force of 20 newtons on each individual surface of the box. And you can see that the force it's applying is not just applying in one specific direction. It's not just applying up or down or left or right. It's applying outward everywhere. So because the forces from the pressure apply in multiple directions, the pressure itself does not have a direction, so it's a scalar, not a vector. Doing math with the pressure equation by itself is very simple. I'm just going to throw out these 4 examples. I'm not even going to talk through them. I'll just display the problem-solving process. There are some pressure problems where you have to calculate the area the pressure is applying to. In problem 3, you're given a circle of radius 5, so you just have to know that the area of a circle is 2 pi times the radius squared. And in example 4, you're given a rectangle with a length of 0.2, and you need to calculate its width. So geometry comes into pressure equations at times. Example number 5 has some more complex geometry, so I want to show you how that works. A solid cylinder of height h and density rho is placed on a flat surface. Show that the pressure P exerted by the cylinder on the surface is equal to rho times g times h. So the pressure is the force over the area, and I know that the force applied by the cylinder, because it's resting on a surface, its force of gravity is pulling it into that surface, so the surface has to support it with that same force. So that means the force it's applying is equal to the mass times the acceleration of gravity. And I know that mass is equal to density times volume because density is equal to mass divided by volume. So if I rearrange that equation, that's what I get. And I know that the volume of a cylinder is equal to the surface area of the base of the cylinder multiplied by the height of the cylinder. So I can now take this volume back and plug it into my mass equation, and then take that mass equation and plug it into my force equation, and then take that force equation and plug it into my pressure equation. And when I do that, I can see that the areas cancel out, and I can see now that the pressure is equal to the density multiplied by the height of the cylinder multiplied by the acceleration of gravity. As a rule, if there's any kind of difference in pressure in gas in a container, gas always flows from a higher pressure to a lower pressure region until the two pressures are equal and the pressure is equally distributed everywhere around the container. We can imagine that gas 1 and gas 2 are in two containers connected by a tube that the gases can move through. If the problem says the gases do not move through the tube, this tells you that they have the same pressure as each other. You can assume, unless otherwise stated, that all regions of a gas always have the exact same pressure as all other regions of a gas. Because pressure is equally distributed, we can use proportional reasoning to find the force applied on different parts of the container of pressurized material. An example here says the area of the top and base of a box is A and the other sides have area 2A. The force from pressure inside the box is 20 newtons on the top of the box. What is the force on any one side of the box? I know that pressure is force over area, so therefore force is equal to pressure times area. So we know that 20 newtons is equal to the pressure inside of the box multiplied by the area of the top or base of the box. And I also know that that pressure is the same everywhere in the box, so it's being distributed to all parts of the area. So if I want to know the force on one of the sides of the box, I can use the same pressure but this new area. And when I isolate my original equation, PA, I can plug in 20 newtons because I know PA by itself is 20 newtons. So altogether, I can see that 40 newtons are applying to any one side of this box. I can use proportional reasoning and the fact that pressure is constant in all parts of the container to predict missing forces on the object. If there's a difference in pressure on two sides of a barrier, we can calculate the force on each side. I can pretend that we're looking at this barrier from the side, and altogether its surface area is 5 meters squared. So the pressure on one side I'm going to say is 10 pascals, and on the other side there's a pressure of 4 pascals. Again, using pressure equals force over area, and rearranging to find force. If I multiply the pressure by the area, I'll get the force applied. So the force applied from the green gas is equal to 20 newtons to the left, and the force applied from the blue gas is equal to 50 newtons to the right. So I can see that the net force on this barrier is 30 newtons to the right. So these forces behave just like other forces. We can add them together to find the net force. A common pressure problem asks how much force it would take to open a door with different pressure on either side. A door is prevented by its frame from opening in one direction. The force required to open the door is equal to the difference between the two forces from the gas pressure. So we can pretend that this barrier is a door. You can see that it has a door frame on one side of it that puts a force on it, preventing it from accelerating to the right. That force perfectly balances out any other forces pushing into it. So altogether the net force is 0, so the door does not accelerate. The door frame is applying this 30 Newton force to the left to prevent the door from moving into the frame. So if we want to open the door, we have to apply a force of pull to at least completely cancel out the force of the door frame, and then add a little bit more to make the net force no longer 0. So if any additional force is applied from this point, the net force will be non-zero and point away from the door frame, and the door will begin to move. Therefore, the force required to make it move is equal to the difference between the forces given by each pressure, which here is equal to 30 newtons. If one pressure is pointing to open the door with 20 newtons, and the other pressure is pointing to keep the door closed with 50 newtons, altogether it would take an additional 30 newtons of pull or more to open the door, but 30 newtons is the minimum required. Air in Earth's atmosphere also has pressure, so if a material is exposed to the air with no barrier between it and the air, atmospheric pressure applies on it. As an example, a tube holds air compressed to a pressure of 1.1 times 10 to the 5th Pascal by a cylinder with a mass of 500 kilograms and a base of 0.5 meters squared. The only thing supporting the cylinder is the pressure from the air, and we want to determine the atmospheric pressure of the air outside the tube. I'll draw a free body diagram to figure this out. So I know that there's the force of gravity on this object pulling it down, which is equal to 4,900 newtons because it's mass times the acceleration of gravity. There's also an upward force from the pressure inside the tube, and that force I know is equal to the pressure times the area, which is equal to 5.5 times 10 to the 4th newtons. And because there's air with pressure above the blue object, that pressure must also be pointing down on the blue object. So that force is going to be equal to the atmospheric pressure of Earth multiplied by the area that it's applying to. I also know that because this mass is not accelerating up or down, it's just standing still, the net force must equal 0 as a result. That means that these three vectors added together have to equal 0. So when I write out the equation like this, I now have an equation with only one missing variable, so I can isolate the pressure of the atmosphere, and when I do that, I get 1.0 times 10 to the 5th Pascal. Those are all the facts about pressure that you'll need to solve problems with just that concept. It's going to become much more important when we start working with the ideal gas law, PV equals nRT, in a later lesson in this unit. This lecture is about the kinetic model of an ideal gas. This is introducing the idea of what an ideal gas is. This is a summary of all the information we'll be going over. And this is the kinetic model of an ideal gas itself. These are all the requirements for a gas to be an ideal gas. As a reminder from a previous lecture, internal energy in particles in a material can be either kinetic energy of the particles or potential energy in the bonds between particles. Adding kinetic energy increases the temperature, and adding potential energy decreases the strength of the bonds between the particles. So both of these are examples of internal energy, energy contained within the particles of an object. If that internal energy is kinetic, it goes into increasing the temperature of the material, and if it's potential, it goes into changing the phase of the material, but doesn't change the temperature. We're now ready to talk about what an ideal gas is and what a non-ideal gas is. So this is the fundamental property of an ideal gas. All internal energy that we add to this gas becomes kinetic energy. So there's a linear relationship between internal energy added and temperature. So if we have an ideal gas, what it means for the gas to be ideal is that if we add any energy to the gas, all of that energy becomes kinetic energy in the particles. And because all of the energy becomes kinetic energy, and adding kinetic energy increases the temperature, any increase in internal energy must also increase the temperature. If you look at my animation on the left, you can see that as I add internal energy to the particles, their velocities go up, and therefore their kinetic energy goes up, and the temperature goes up. And this is just consistent no matter how much internal energy I add. There's never a point where that internal energy does not also add to the temperature. So this means there's a linear relationship between the internal energy and the temperature. If I add more to one, I add more to the other as well. If a gas meets that property, if all the energy added goes into kinetic energy of the particles, we say that that is an ideal gas. That's what we mean by an ideal gas. In comparison, in a non-ideal gas, some internal energy added becomes potential energy in the bonds between particles, so there is a nonlinear relationship between internal energy added and temperature. So if I start to add internal energy to this non-ideal gas, some of it becomes kinetic energy, but some of it may randomly go into the bonds between particles instead. And I can't predict whether the internal energy will become kinetic energy or potential energy. Watching that animation again, you can see that as I add internal energy, it's going into kinetic, but then it randomly decides to go into potential and then adds a little more into kinetic. But the relationship between the internal energy added and the kinetic energy of the gas is not linear. If I increase the internal energy, it does not necessarily increase the kinetic energy. A non-ideal gas is more difficult to predict in that way because we can't know what the energy will do when we add it to the non-ideal gas. So that's why we call it non-ideal, because in an ideal world, a gas would be very easy to predict and understand. So a non-ideal gas is more difficult to predict because we don't know what the energy will do when we add it to the gas. Just to reinforce this a little bit more, in an ideal gas, all of the energy added becomes kinetic, and in the non-ideal gas, the energy can either become kinetic energy or it can become potential energy and break down the bonds between particles. So that leads to the question, what properties must an ideal gas have so that all energy added becomes and remains kinetic energy in the particles? There's a whole list of properties, but these are the two properties that it's most important for an ideal gas to have so that all the energy added becomes kinetic energy. The first property is there can be no intermolecular forces or bonds between the particles. If there were intermolecular forces or bonds between particles, some of the energy added would go into breaking up those bonds. It would become potential energy instead of increasing the velocity of the particles, which increases the kinetic energy. So a situation where there are no bonds at all between the particles that means this could be an ideal gas. And if there are intermolecular bonds, that's bad. And that means that this is not an ideal gas. The second requirement for all the energy to become kinetic energy is that all collisions between particles and between particles and the barrier must be perfectly elastic. Because perfectly elastic collisions are the only type of collision where the total kinetic energy remains constant. If an inelastic collision occurred, some kinetic energy would be lost from the gas. So if the particles are colliding, they have to have a perfectly elastic collision. They can't stick together at all. And if the particle collides with the barrier that's holding the gas, it also can't stick to the barrier at all. It has to be perfectly elastic and bounce back in the opposite direction. If any kind of inelastic collision occurs, some kinetic energy is converted to other types of energy, and it no longer exists as kinetic in the gas, which means that the energy added wouldn't necessarily remain kinetic energy. There's a common comparison made between particles in an ideal gas and billiard balls. Particles in an ideal gas behave just like billiard balls rolling on a table. There are no forces holding them together, they just kind of roll in random directions. So because there are no forces holding them together, they meet that first requirement for an ideal gas, and all of their collisions are also perfectly elastic. They always bounce off each other and never stick together, and never stick to the edge of the table either. So if you're having trouble remembering the properties of an ideal gas, the billiard ball example might help. The particles behave just like they were a ton of billiard balls bouncing off each other. So again, the reason why we call this the kinetic model of an ideal gas is that it's saying that the fundamental reason we call gas ideal is because of something related to kinetic energy. All the energy going into it has to be kinetic energy. There are implications of these assumptions, and you're expected to memorize these properties of an ideal gas for this course and for the IB test. I won't read these all out, but these are the properties of an ideal gas that you're expected to memorize for this class. All gases in the real world are non-ideal. There's no such thing as a real, true ideal gas, which means the particles in them have some intermolecular forces, and some of the collisions of the particles are not perfectly elastic. Gases behave more like ideal gases when the particles have a lot of kinetic energy compared to potential energy, because most of the energy going in becomes kinetic rather than potential. This occurs at lower pressures, lower densities, and higher temperatures of the gas. The more a gas behaves like an ideal gas, the more easy it is to predict its behavior mathematically. So the more that a gas has these properties, the better that is for us as scientists, because we want the gas to be more predictable and understandable. So if the gas has more kinetic and less potential energy, it behaves more like an ideal gas. And if it has less pressure, more temperature, and less density, it also behaves like an ideal gas. This is because higher temperatures mean more kinetic energy, and lower pressure and density means the particles are interacting with each other less and thus not applying as many intermolecular forces. This is another common test question where you are expected to know the situations where a gas behaves as an ideal gas. So again, that's when the particles have more kinetic energy, less potential energy, less pressure, more temperature, and less density. Those are the conditions for a gas to behave more like an ideal gas, which is easier to understand and predict. So that's everything that you need to know about the kinetic model of an ideal gas. This is a summary of everything that I talked about. And again, this is a list of the properties of an ideal gas as implied by the kinetic model that you're expected to memorize and understand for the rest of the course. This lecture is about the ideal gas law, PV equals nRT. This lecture is assuming that you already know what an ideal gas is. It's a gas where all internal energy added goes into kinetic energy and thus changes the temperature. So internal energy and temperature are linearly related in an ideal gas. This definition is explained in a previous lecture that I've linked in the description. This lecture is specifically focused on this equation, PV equals nRT, which we call the ideal gas law because it's true for any and every ideal gas. This equation is always true if we're dealing with a gas where the only type of internal energy present is kinetic energy. This video will exist in 3 parts. In the first part, I'll walk you through the meaning of each variable and some tricks to finding them. In the second part, I'll go over some relationships that exist between the variables. And in the last part of the video, I'll conclude with a ton of examples for using this equation in different types of problem solving, whether it's plugging stuff in, using graphs, or using proportional reasoning. This is the meaning of each variable in the ideal gas law. I'm going to go into each one in more detail, but for now you can see that the ideal gas law is telling us that the pressure applied by the gas multiplied by the volume that contains the gas is equal to the number of moles of gas times the ideal gas constant times the absolute temperature of the gas. We know that pressure is equal to the force applied per area along the container of the gas, and its unit is Newton per meter squared or pascals. We covered this in a previous lecture that I'll link in the description, and you're actually expected to remember a lot of properties of pressure from that lecture in order to be able to use the ideal gas law. I'm not going to repeat myself from that previous lecture on all the properties of pressure, so if you haven't watched that previous lecture, you'll want to start there just because I'm going to be using those properties of pressure in some of the problem solving later, and you'll definitely be expected to be able to do that in worksheets, labs, and tests in this course. This is some new information about pressure that you need to know for the ideal gas law. All collisions in an ideal gas are perfectly elastic. Pressure from an ideal gas comes from the impulse of the particles on the container. Because all the collisions are elastic, when the particles hit the container wall, the wall applies a force on the particle, and the particle applies a force back on the wall. So that force on the wall is the force in the pressure equation, and the area is just the area of the wall. So the reason why gas has pressure is that the particles in the gas are constantly bouncing up against the wall of the container of gas, and are thus applying a force on the wall, and are therefore applying pressure on the wall. The next variable to worry about is volume. That's just the 3D volume that the gas occupies. And some problems will require you to calculate the volume of different three-dimensional shapes, so I've left the equations for a few common volumes in the bottom right. The next variable is n, which means the number of moles of gas. As a reminder, there are 2 ways to calculate how many moles are present. You can either divide the mass of the gas by the molar mass of the element, or the number of particles present by Avogadro's constant. So the unit for n is mole, because it's a measurement of how many moles there are. And remember, Avogadro's constant is 6.02 times 10 to the 23rd particles per mole. This just means there are that many particles of an element in 1 mole of that element. I'll give you an example of the 2 ways to find the number of moles in a gas. So if you're given the mass and the element of the gas, as an example, how many moles are in 5 kilograms of oxygen, you would start by using the periodic table to find the molar mass of the element. That can always be found at the bottom of the element's label on the periodic table. So I can see that the molar mass of oxygen is about 16, and that molar mass on the periodic table is always written in terms of grams per mole. So that number means there are 16 grams per mole of oxygen. The second step is to divide the mass of the gas by the molar mass of the element and to make sure that the mass units match. So because this is 5 kilograms of oxygen, I'm going to convert that to grams just so it matches up with the grams in the molar mass. So that's equal to 5,000 grams. I divide the mass of the gas by the molar mass of the element, and when I do that, I find that 5 kilograms of oxygen contain 313 moles of oxygen. So that's how you would find lowercase n if you were dealing with a problem like this with an ideal gas law question. If you're given the number of particles in the gas, you just divide the number of particles by Avogadro's constant, 6.02 times 10 to the 23rd particles per mole. If I wanted to know how many moles does a gas contain if there are 8 times 10 to the 25 particles, I would just divide the number of particles by Avogadro's constant, and I end up with 133 moles. So that's how you find lowercase n in the equation if you have to calculate it. The IB Physics data booklet writes the equation for n like this: lowercase n is equal to uppercase n over uppercase n subscript a. Uppercase n is just the number of particles in the gas, and uppercase n subscript a is Avogadro's constant. And Avogadro's constant is also given in the IB booklet. So you'll never have to memorize that on a test. The next part of the ideal gas law is capital R, and this is just a constant. This is just 8.31 joules per mole Kelvin. It's just a specific relationship that exists to balance out the units that we use. It doesn't really mean anything else. It's just a number that you always have to put into the ideal gas law. The last variable to worry about is capital T, which is the absolute temperature. It's not just the temperature. We call it the absolute temperature because it's only measured in Kelvin, not degrees Celsius or Fahrenheit. An absolute scale is a measurement system where the 0 value is where there is actually none of the quantity being measured. So as an example of an absolute scale, if I said I am 80 years old, that means I am 80 years away from being 0 years old, from having no age at all. So that would be an absolute scale because the 0 point on that scale is where I actually have none of the thing being measured. In comparison, I am 3 years older than before is a relative scale because at the 0 point of that scale, I am 0 years older than I was before. That doesn't mean I have 0 years of age. It could be at any age where I start. It's totally relative where I start, and I begin increasing from 0 from that point, even though my actual age is not 0. That's an example of a relative scale. The Kelvin scale is an absolute scale, and the Fahrenheit and Celsius scales are relative. What this means is that at 0 degree Kelvin, there is literally no temperature. Temperature is just a measurement of the random motion of particles, and at 0 degrees Kelvin, there is literally no random motion of the particles at all. So the 0 point of the scale is where there is actually 0 of the thing it's measuring. At the 0 point on the Celsius scale, there is still some motion of the particles, so Celsius is a relative scale, so we can't use it in the ideal gas law because the 0 point still has some movement. And you might ask yourself, why is it so important that we use this absolute scale? How does that affect the equation? Well, we can use the math of this equation and what we understand about the variables to understand why temperature has to be absolute. Let's imagine that we have 0 temperature. We don't know whether we're using Celsius or Kelvin. I'm just going to say the temperature is 0. If the temperature of the gas is 0, and I assume that the volume is not 0, it's a normal volume, the only way for this equation to be true is if the left side is also equal to 0. So that means that the pressure must be 0 whenever the temperature of the gas is 0. This has to be true, and if that's not true, if the temperature were 0, but the pressure were somehow not 0, this equation would break down, because it would say a non-zero number on the left is equal to a 0 number on the right. So when temperature is 0, pressure has to be 0 as well. And I remember that pressure comes from particles hitting the sides of the container. And they can only do that if they're moving. If the particles are not moving at all, they're not going to have any collisions with the sides of the container, so there won't be any pressure. So the only way for there to be no pressure is if the particles are not moving at all, which happens at a temperature of 0 Kelvin. So if we use the Kelvin scale for T, that works, because at 0 Kelvin, there is actually 0 pressure because the particles don't hit the wall. If we use Celsius instead, I remember that at 0 degrees Celsius, it is not the case that the particles are standing still. They still have some random motion. And if they still have some random motion, that means that the pressure will not be equal to 0 because the particles will be randomly bumping up against the side of the container and putting a non-zero force on the container, so there will be pressure. So if we say that it's okay to use Celsius for the temperature in the ideal gas law, that would mean that the right side could equal 0 while the left side does not equal 0, and that would cause the equation to not work. So that's why for this equation we always have to use Kelvin, never Celsius. That's a summary of the meaning of each variable in the ideal gas law. You'll notice that this equation only works when dealing with an ideal gas. The equation itself actually implies that the gas is ideal. Remember that the definition of an ideal gas is there's a linear relationship between internal energy and temperature. I notice on the left I have pressure times volume, and I know that the unit of pressure is a Newton per meter squared, and the unit of volume is a meter cubed. So when I multiply pressure times volume, as I do on the left, I get these variables, which come together to make a Newton meter, which is equal to a joule, which I know is a unit of energy. So pressure times volume actually has units of energy. That's not going to be energy by itself, it's actually going to be some constant, and we don't know exactly what that constant is, but it's not changing the unit at all. So we know that the energy multiplied by some constant that I don't understand is equal to nRT, and if we assume the amount of gas is staying the same, n times r is also a constant, and I'm left with a linear relationship between the energy and the temperature. It literally fits the linear equation y equals m times x. So because this is linear, this is definitely an ideal gas, and because it's an ideal gas, it's linear. That's why this equation only works when we're dealing with an ideal gas, because if we were working with a non-ideal gas, some of that energy would go into breaking the bonds between particles, and it wouldn't affect the temperature, and the left side would get a different value than the right side. And this is also the reason why we care about whether a gas is an ideal gas. This is why we came up with that definition of an ideal gas. If we model a gas as ideal, we are allowed to use this equation to predict the gas's behavior, and we can do that better the more the gas behaves like an ideal gas, the more it fits this equation. A lot of questions come up about graphing different parts of the ideal gas law. Because there are so many variables, we usually hold some of them constant and graph other variables. For all three of these graphs, I'm going to pretend that lowercase n is a constant. The amount of gas being graphed is remaining the same. If I construct a graph of pressure versus time and I hold the volume constant, I can predict what that graph will look like using the equation itself. I've written all the constants in black, so when I rearrange this equation to get the y value on one side and the x value times a constant on the other, I can see that this fits a linear pattern where pressure is the y value, temperature is the x value, and the slope is nr over v, and the y-intercept is 0. So this fits a linear pattern, and this is what that graph would look like as a result, and this would be the slope. So what this graph is physically showing is a situation where we are holding the volume constant, but increasing the temperature and observing what happens to pressure. And if we increase the temperature of the gas in the container, those particles are going to get faster and faster because temperature is a measurement of the average kinetic energy of particles. And if I make the particles go faster by increasing the temperature, they're going to hit the walls of the container harder and make the force bigger on the container and therefore increase the pressure. So as I go up this graph, you can see that as I increase the temperature, the force increases and therefore the pressure on the walls increase. So that's what that graph is physically showing us about the gas. We can also hold pressure constant and make a volume versus temperature graph. Rearranging PV equals nRT to get V on one side, I get this equation, which I can see also fits a linear form, where the slope is nr over pressure, and the y-intercept is 0. So I'll draw that line out. So this is the slope of that graph. And to build your intuition here, what's happening here is that I'm increasing the temperature, but while I'm doing that, I'm trying to change the volume in the exact way that keeps the pressure constant, because we're holding the pressure constant in the second example. So because pressure is equal to force over area, I know that the force of the particles hitting the wall will increase when I increase the temperature because they'll be moving faster. So in order to keep pressure constant, I'll have to increase the size of the area they're impacting as well. So if I start with a low temperature and low volume, and then increase the temperature while holding the pressure constant, I have to increase the area that they're impacting as well, and so the volume increases. That's what that second graph is showing us. On the third graph, we're holding temperature constant and graphing pressure versus volume. So when I write this out, PV equals nRT and isolate P, I can see that this actually fits an inverse form because this is measuring 1 over x. So this graph is an inverse shape like this. This is showing a situation where the pressure starts off very high and we're keeping the temperature constant. We're not increasing the velocity of the particles. If we don't increase the temperature, that means the force applied by the particles will remain constant as well. And if we increase the volume, the area that they impact is going to become larger. So if we hold F constant and make A larger, you can see that as a result, the pressure shrinks, just like it shows it doing on the graph. So as the volume increases, the pressure decreases, as long as we're holding the temperature constant. One last note about graphing. If we did measure temperature in degrees Celsius, 0 degrees Celsius would still have a non-zero pressure because the particles would still be moving. So a pressure-temperature graph with Celsius as the unit of temperature would look something like this with a non-zero y-intercept. Because at 0 degrees Celsius, there would still be a non-zero pressure. This is the last part of the video where I'll do example problems in graphing, math, and proportional reasoning. These are two example graph problems. An ideal gas of constant mass is held at a constant pressure P. This graph shows the volume V of the gas as it varies with constant temperature T. What is the slope of the graph? Well, I know PV equals nRT, so isolating the Y and the X, I can see that they fit this form. So the constant taking the place of the slope is nR over P. That would be the slope of the graph, and that's the answer to the question. Example number 2 says the graph below shows the pressure of a gas on the y-axis and the inverse of the volume on the x-axis. The graph is at a constant temperature. Determine the slope of the graph, including the correct unit of slope. We'll start with part A, determine the slope of the graph, including the correct unit of slope. I know that slope is rise over run. I can see 2 points on the graph that I'll compare. That's the slope of the graph. I just read the numbers and units off of the graph. And I remember from a previous part of this lecture that a Pascal times a meter cubed is equal to a joule. The reason why is that a Pascal times a meter cubed is equal to a Newton over meter squared times meters cubed, which is equal to a Newton meter, which is equal to a joule. Part B says the temperature of the gas is 330 Kelvin. Determine the number of moles of gas present. So PV equals nRT. Rearranging this to get the equation for the graph, I can use this to isolate the parts of the equation that go with the slope. Because v to the -1 is my x-axis and p is my y-axis, I can see that the slope must be equal to n times r times t. So n is equal to the slope over rt. I can plug in what I know about the slope. R is always a constant, and 330 Kelvin I get from the problem. And when I calculate that out, that's equal to 18.2 moles of gas present based on the properties of this graph. These next two examples are math problems instead of graph problems. In example 1, 20 kilograms of argon gas is heated to a temperature of 30 degrees Celsius. If the gas is contained in a cylinder of radius 2 meters and height 0.5 meters, what is the pressure of the gas? I don't even think about it, I just start writing down what I know. The volume is the volume of a cylinder, so this is the equation for that. So the total volume is 6.3 meters cubed. To calculate the number of moles, I can divide the mass of the gas by the molar mass. And I can see that argon has a molar mass of about 40 if I look at the periodic table. So that's 40 grams per mole. So to make this convertible, I convert the mass into grams instead of kilograms. And when I do that division, I find that there are 500 moles present in this gas. R is always that same constant no matter what. And T is 30 degrees Celsius, but I need that measured in Kelvin. So I add 273 to get 303 Kelvin. To find the pressure, I just use the equation and isolate P, so I divided both sides by V. And when I plug in all the numbers that I have, I get a pressure of 2 times 10 to the 5th pascals. So that's how you would solve a math problem using PV equals nRT. Example 2 is more complex. For example 2, I'm going to be using some of the properties that we learned about in the pressure lecture. So again, definitely refer back to that in the description of the video if you haven't watched it yet. The air in a kitchen has pressure 1 times 10 to the 5th pascals and temperature 25 degrees Celsius. A refrigerator has an internal volume of 0.36 meters cubed. The door of the refrigerator is closed and the air inside is cooled to 4 degrees Celsius, and the number of air molecules stays the same. In part A, when the door is open, the air inside the refrigerator is at the same temperature as the kitchen. Calculate the number of air molecules in the refrigerator. I know that the pressure inside the refrigerator is the same as outside when the door is open because pressure is always equal when there isn't a barrier between the two gases. The volume of the refrigerator is 0.36, and the temperature is 25 degrees Celsius, which I need in Kelvin. So that's 298 Kelvin. And I need to know lowercase n before I can calculate the number of air molecules. And R is always that same number. I can plug that into PV equals nRT, so n is equal to this equation. And when I plug in my values, I get 14.5 moles. But I need to know how many particles there are. So the number of moles is equal to the number of particles over Avogadro's number. So when I multiply both sides by Avogadro's number, I get a number of particles equal to 8.73 times 10 to the 24th. That's how many particles of air there are in the refrigerator. Part B says to calculate the pressure inside the refrigerator after the air is cooled. So we're dealing with a new temperature. We know the volume is the same. The temperature is now 4 degrees Celsius, which is equal to 277 Kelvin, and lowercase n is 14.5 moles. There's no air leaving the refrigerator after the door is closed, so we can use that same answer from part A. R is the same, that's always that constant, and we're trying to find the pressure. So I'll rearrange the equation to get pressure by itself, and plugging in my numbers gets me 9.27 times 10 to the 4th pascals. Part C says the refrigerator door has an area of 0.8 meters squared. what is the minimum force needed to open the door? You'll remember from the pressure lecture that we need to understand the force on both sides of the door before we can understand how much force it takes to open the door. The pressure on one side, the outside, is 1 times 10 to the 5th pascals, and on the other side from the previous answer is 9.27 times 10 to the 4th pascals. Rearranging the pressure equation gets me force equals pressure times area. So the force from the outside is 8 times 10 to the 4th newtons, and the force from the inside is 7.42 times 10 to the 4th newtons. So the force required to open the door, as you'll remember from the pressure lecture, is the difference between those two forces. So the difference between those two forces is going to be equal to 5.8 times 10 to the 3rd newtons. So that's how much force you would have to apply to open the door of the refrigerator after it had been sealed and the air had been lowered to that lower temperature. Finally, I'll close out with 4 proportional reasoning problems. I'm doing more of these just because they're a very common type of test question. In example 1, 2 containers A and B contain an ideal gas and are connected with a tube of negligible mass. The volume of A is 3 times that of B. A is at a temperature of 100 Kelvin and B is at a temperature of 400 Kelvin. What is the ratio of the mass of gas in A to the mass of gas in B? To start off, we know that because the gases aren't moving between the containers, that their pressures are the same. Because gas always flows from a high pressure to a low pressure area, so if that's not happening, the two pressures must be equal. I know the temperature of A and the temperature of B, and the volume of A is 3 times the volume of B, and I can use PV equals nRT to relate these, and I'm trying to compare the mass, which I know has something to do with the number of moles, so I'll rearrange to isolate the number of moles. The number of moles in A is equal to this, and the number of moles in B is equal to this, just based on the variables that I have. I know that the number of moles is equal to the mass over the molar mass, so therefore the mass by itself is the number of moles times the molar mass. So this is the mass of A, and this is the mass of B. And this is the ratio between them because that's what we're trying to find. And the molar masses are the same because it's the same gas, so it's the same element. So that means I can cancel out the molar mass, and I'm just left with Na over Nb. So Na over Nb is equal to the mass of A over the mass of B, so that will be the answer to my problem if I can write that out as a number. So I rewrite that using the equations I have for Na and Nb, and I'll write those equations entirely in terms of the variables for B. I know that the pressure of A is equal to the pressure of B, and the volume of A is equal to 3 times the volume of B, so I can replace those. And I also have 1 over 100 over 1 over 400, which is just equal to 4 in the numerator. And I can now cancel a bunch of stuff out because there's a lot that appears in the numerator and denominator, and when I cancel that out, I get a final answer of 12. So the ratio of mass A to mass B is 12. There's 12 times as much mass in container A as in container B. In example 2, a tank of fixed volume V contains N molecules of an ideal gas at temperature T. The pressure at Kelvin temperature T is 30 megapascals. N over 3 molecules are removed, and the temperature changes to 2T. What is the new pressure of the gas? As an answer, the original pressure, P1, is equal to these values, and I know that's equal to 30 megapascals. Pressure 2 has 2/3 of the molecules of pressure 1, and the temperature is twice as high, so I've written those values in. If I can isolate my original values in that new equation, I'll understand how the new pressure relates to the old pressure. So if I bring up those numbers, if I bring up that 2 to one side, I get 4/3 times those original values. So that means this is equal to 4/3 times P1, which is equal to 4/3 times 30 megapascals, which is just equal to 40 megapascals. So that's the new pressure of the gas. In example 3, container A contains 2 moles of an ideal gas, and container B contains 4 moles of the same ideal gas. B has 5 times the volume of A. The pressure in A is 2 times the pressure of B. What is the ratio of the temperature of gas A to the temperature of gas B? So as an answer, PV equals nRT. I'll isolate T by itself because I'm taking the ratio of temperatures. I know that the number of moles in A is 2, and the number of moles in B is 4. And the volume of B is 5 times the volume of A, and the pressure of A is 2 times the pressure of B. So this is the equation for the temperature A, and this is the equation for the temperature B. So TA over TB is equal to this, and I can now rewrite some variables as other variables and start to cancel things out. So I know that PA is equal to 2PB, so I'll just replace all the A's with B variables. Because VB is 5VA, VA is equal to 0.2 VB. And I know that NA is 2 and NB is 4, so if I take 1 over 2 over 1 over 4, I get 2 in the numerator as a result. And when I multiply those out and cancel out the variables, I get 0.8. So that's the ratio of the temperature of container A to container B. Finally, in example 4, a fixed mass of an ideal gas in a closed container with a movable piston initially occupies a volume V. The position of the piston is changed so that the temperature of the gas doubles and the pressure remains the same. What is the new volume of the gas? PV equals nRT. And I want to understand the relationship between volumes, so I start by isolating that. The amount of gas is the same, so the moles are the same. The new temperature 2 is double temperature 1. The pressures are the same. So now I can compare V1 and V2. And the problem just refers to this original volume as V. This is V2. And I can rewrite the V2 variables in terms of the V1 variables. The number of moles are the same. T2 is equal to 2 times T1, and the pressures are also the same. I can now isolate my equation for V1 by itself, so I get 2 times that equation for V1. So that means that the new volume is twice as large as the original volume. That's how you do proportional reasoning problems, and that's how you do all types of problems that appear in IB for the ideal gas law, PV equals nRT. This lecture is about the average kinetic energy per molecule of a gas. This is the specific equation that helps us calculate the average kinetic energy for every molecule in a gas. I'll have a separate lecture where I explain where this equation comes from, but the high school IB physics course does not expect you to be able to prove the equation. So for this lecture, I'll just take it as a given. I can see that the average kinetic energy is equal to 3/2 times Kb, which stands for the Boltzmann constant. It's a specific constant multiplied by the temperature. And it's also equal to 3/2 times the ideal gas constant over Avogadro's number, again multiplied by the temperature. I can see that this implies that this new number, Boltzmann's constant, is equal to the ideal gas constant over Avogadro's number. I'll show you how to use this equation in a minute. I just need to clarify some of the variables. So the average kinetic energy is not the total kinetic energy in the gas, it's the total kinetic energy divided by the number of particles. So it's literally the average kinetic energy per particle. As an example, if we take this box on the right, I can see I have a particle with 5 joules, 1 joule, 8 joules, and 6 joules. So the total kinetic energy is 20 joules, but there are 4 particles. So that means that the average is the total kinetic over the number of particles, which is equal to 5 joules per particle. So that would be the average kinetic energy per particle in that gas. That's what that variable is referring to. Because this is an ideal gas, all the energy is kinetic, so the total kinetic energy is the total internal energy in the gas. Sometimes IB questions ask you to calculate the total internal energy in an ideal gas, and they always mean the total kinetic energy, because in an ideal gas, all the energy exists as kinetic energy. This equation can be a bridge between the ideal gas law and the average kinetic energy equation. If you're given the total internal energy of the material, you can connect the equations using this pattern. So if I have PV equals nRT, I can use that to find N, and I can use N to find the number of particles in the gas, and I can use the number of particles in the gas along with the total internal energy to calculate the average kinetic energy and set that equal to 3/2 times Boltzmann's constant times the temperature. So you can go from one to the other if you have the total internal energy of the gas. We can use the kinetic energy equation along with the average kinetic energy equation to find the average velocity of particles in a material. Because kinetic energy is 1/2 mv squared, the average kinetic energy is going to be 1/2 times the mass of any one particle times the average velocity of all the particles squared. Remember that we assume in an ideal gas that all particles have the same mass, so we could say the average mass of all the particles, but we're assuming that all the masses are the same, so that's just the mass of any one particle. As an example, the temperature of argon gas is 330 Kelvin. What is the average velocity of each particle of the gas? So I know the temperature is 330 Kelvin. This is Boltzmann's constant. And the mass of a particle is equal to the material's molar mass divided by Avogadro's constant. That's the mass of one individual particle of a material. I can see that the molar mass of argon is about 40. It's at the bottom of its symbol on the periodic table. So that means that the molar mass is 40 grams per mole, and I put that over Avogadro's constant to get this mass of any one particle of argon. And I want to convert this to kilograms because that's the mass that we use in the kinetic energy equation. So I divide that by 1,000 and get 6.6 times 10 to the negative 26th kilograms. This is the equation for the average velocity. I just rearranged the average kinetic energy equation. And when I plug in my other equation for kinetic energy, 3/2 times Boltzmann's constant times temperature, this is what I get. Plugging in the numbers that I'm given, I get a final answer of 455 meters per second. So that would be the average velocity of any one of the particles in the gas. This equation only works for an ideal gas because, again, there is a linear relationship between the total kinetic energy and the temperature. You can see using y equals mx that fits that same linear form. So this equation also only works when we're dealing with ideal gases. Using the equation on its own is pretty simple. I'll finish with two example problems. In example 1, the average kinetic energy of a gas is 9.32 times 10 to the negative 20th joules. What is the temperature of the gas in degrees Celsius? So I have the average kinetic energy. I'm always given Boltzmann's constant. This is also in your IB packet. So plugging these into my equation and rearranging to find the temperature gets me 4,500 Kelvin. And because this is asking for degrees Celsius, I need to subtract 273 degrees. So this is actually equal to 4,227 degrees Celsius. In example 2, helium gas is contained in a volume of 3.5 times 10 to the negative 4th meters cubed at a temperature of 300 Kelvin and pressure 5 times 10 to the 5th Pascal. Calculate in joules the internal energy of the helium. So this is the volume, and this is the temperature, and this is the pressure. Boltzmann's constant. And we use this notation for the number of particles, capital N. And I know that lowercase n, the number of moles, is equal to the number of particles over Avogadro's constant. And this is Avogadro's constant. And this is the ideal gas constant. So I'm just writing down everything I know because this is actually going to require me to use both the ideal gas law and the average kinetic energy formula. So the total internal energy is equal to the average kinetic energy multiplied by the number of particles. And I know that the number of particles is equal to the number of moles multiplied by Avogadro's constant. So I'll replace that in my equation. And the average kinetic energy is equal to 3/2 times Boltzmann's constant times temperature. And rearranging PV equals nRT for N gets me this. And so when I plug all these in, I'll be able to get an equation with only the variables that I already know. So this is a lot, but I know the value of every single one of these variables, so I can plug in those values, and when I do that, I get a final answer of 262 joules, so that's the total internal energy of the helium. And that's how you use the average kinetic energy per molecule equation to solve problems.
This video is about current and drift velocity. Current is a measurement of the amount of charge passing by a point per unit of time, and it's a scalar. The variable for current is capital I, and the unit is capital A, which stands for ampere. We also just call that amps, so we can say like 5 amps of current. The equation is current is equal to charge per time, because again, it's the amount of charge passing per unit time for a given location. As an example, if I draw this line and imagine that 10 coulombs of charge pass by the line in 2 seconds, the current there was 5 amps, 5 coulombs per second. So that's what an amp is, and that's what current is. It's pretty simple, just a measurement of how much charge is passing in a given amount of time. Current has a direction, but it is not a vector. This is because it doesn't obey the rules of vector addition. So you can't really use trig or triangle math or anything like that, or connecting the tip to tail to understand current. So because it doesn't work that way, we say that it's not really a vector. And almost all current is the result of electrons moving in a material. So it would make sense to say that the direction of current is the direction that electrons are moving inside the material, which is the direction negative charges are moving. This direction is the real direction of current. So like if you have a wire going in a circle and you have current in the wire, the actual movement of the electrons is the movement of negative charge. It has a certain direction associated with it. So we could say that that's the direction of the current. That's the real direction of the current. However, there's something weird about how we talk about current, which is that the concept of current and all our physics around it was invented before we knew about electrons, before we specifically knew what electrons were and how they worked. So scientists at the time decided that current is the direction of the movement of positive charges. So even though positive charges are not actually moving in a circuit or in most other situations, we can say that because the negative charges are moving away from that area, it's kind of like the positive charge is moving toward that area. So that opposite direction of the negative charge, the positive charge, we call this direction the conventional current, a direction we use because of convention, not because it represents reality. The math in this course is based around conventional current, not the real direction of current. So whenever you see current symbolized as moving a certain way, you'll know that secretly the electrons are actually moving in the opposite direction, but because of convention and because we've set all the other math up to work with that conventional current, we're going to pretend it points in that direction. There are a few variables that can affect the size of the current in a traditional circuit where electrons are flowing. They're summarized in this second equation for current. So current can be equal to the electrons per meter cubed in a material times the cross-sectional area of that material times the drift velocity of the charges in the material, and drift velocity is just a complex name for saying how fast the charges are moving in that material, times the charge of each carrier moving through the material. That's almost always going to be electrons, because electrons are the only real carriers of charge in most materials. As an example, this is what a typical problem with that second equation could look like. A current of 2 amps passes through a copper wire, and copper wire has 8.5 times 10 to the 28th electrons per cubic meter of cross-sectional area of 0.02 meters squared. What is the drift speed of each charge? So plugging this into my equation, I know the current, I know the number of electrons per meter cubed, I know the area, the cross-sectional area, and I know the charge of 1 electron is that elementary charge. Plugging these in to solve for v, the drift speed, the drift velocity, gets me a drift velocity of 7.3 times 10 to the negative 9th meters per second. So that's how you would use the second equation for current. This video is about voltage, and voltage is a very kind of tricky, very specific idea in physics, but I think if I give you a few pictures and a few examples, it'll make sense. Voltage is a measurement of the electrical potential energy per unit charge between 2 points in an electric field. It is a scalar. Voltage tells you how much energy will be added to a charge as it moves a given distance in an electric field based on the amount of charge. So that kind of makes sense so far. Potential energy in general tells you how much energy something will gain as it moves through a field, like gravitational potential energy tells you how much energy an object will gain by falling through a gravitational field. So in the same way, voltage tells you the electrical potential energy that something will gain in an electric field, but it's not just the electrical potential energy, it's the potential energy per unit of charge. The variable is capital V, and the unit is also V for volts. And the equation is V is equal to work divided by the charge. So I'm going to imagine that I have these 2 parallel plates separated by 10 meters. And you'll remember from the video on electric fields that if you have these 2 parallel plates of opposite and equal magnitudes of charge, the electric field between them will be constant, and it will go from the positive to the negative. I'm going to imagine here that the electric field is 10 newtons per coulomb just for this example. And again, you can see that they're separated by a distance of 10 meters. So let's try to figure out what the voltage is across those 10 meters of distance, because again, the definition says that voltage is the electrical potential energy per charge between 2 points. So to start off, I'm going to say that my 2 points are from the positive plate to the negative plate, the full 10 meters of distance. So to figure out the voltage, I'm going to place a charge at the very beginning of that range. I'm going to say this is positive 2 coulombs, and I'm going to observe how much energy it gains as it moves through the field. So to know the energy, I remember that work is equal to how much energy is going to be added, the change in energy, and work is also equal to force times distance. So if I can find the force on this charge, I can multiply it by the distance and find the work done, and then divide that by the charge to find the voltage. And I remember that the force that a field provides is equal to the charge times the field. So here that's going to be 20 newtons. So 20 newtons of force are constantly acting on this 2 coulomb charge. And because this is positive, it points in the direction of the field. So I'm going to allow this charge to move through the electric field the full 10 meters and observe what happens. Okay, so the field has applied 20 newtons of force on this object for 10 meters of distance. And because work is equal to force times distance, it's equal to 20 newtons times 10 meters, which is equal to 200 joules of energy. So the field added 200 joules of energy to this 2 coulomb charge. So to figure out the voltage, I just need to divide the work done by the field by the charge that it was done on. So when I calculate that, I find that the voltage is equal to 100. So that means that the voltage across those 10 meters in the field is 100 volts. That means that 100 joules will be added to the object for every coulomb of charge that it has. So here, 200 joules were added, 100 for each unit of charge. So regardless of which specific charge is experiencing the voltage, we can still say that the voltage across this 10 meters is 100. And just to prove that to you, I can do this with a different charge. This time I'll use positive 50 coulombs. And I can see if the positive 50 coulombs is pushed along the field, it's going to be pushed with 500 newtons because the field is 10 newtons per coulomb. And so as it's pushed, the amount of work done here will be equal to 500 newtons times the 10 meters that it's pushed for. So the voltage, again, is equal to the work done over the charge, and you can see here that the voltage actually stayed constant at 100 volts. So it doesn't matter which charge we're testing in the field still has this inherent property as long as we're measuring it along that specific distance. If we measured a different distance, like if we just measured this as it moved 6 meters within the field, that's going to have a different voltage because, again, voltage is the change in electrical potential energy per unit charge between 2 points that we select. So our original 2 points were those 2 parallel plates, but now I've selected 2 different points, just 2 random points in the center of the field that are separated by 6 meters along the field. So when I observe how it moves in those 6 meters, I can see that the work done is going to be 500 newtons times 6 meters, which is equal to 3,000 joules. Calculating the voltage from that gets me 60 volts. So across those 6 meters within the field, there are 60 volts of voltage. So the amount of voltage depends on the length that you are moving through the field. The voltage in a field can be calculated independently of the charge experiencing it. This is because voltage is equal to work over charge, and if you have a constant field that isn't changing as you move through it, the work done by the constant field is going to be equal to the force that the field applies times the distance that it's applied for, and the force that the field applies is equal to the charge times the electric field. So that's going to be equal to the charge times the field times the distance traveled. If we plug that back into our voltage equation, we can see that the charges cancel out, and we're just left with voltage is equal to the electric field times the distance traveled in the field. The last thing to know about voltage is that it has some of the most confusing terminology in physics. There's one very specific definition of voltage that sounds very similar to another related idea, but it's actually very different. So these are the 2 phrases that I want you to focus on and focus on how they're different from each other. The phrase electrical potential energy is actually different from electrical potential. So if you see electrical potential energy written somewhere, it's asking for something different than electrical potential. We also call electrical potential potential difference. So electrical potential energy means the work a field can do on a charge. It's basically the amount of energy that a certain section of the field can add to a charge, and it's measured in joules. So it's just that force times that distance. Whereas the electrical potential is the work that the field can do per unit charge. So electrical potential, or potential difference between 2 points, is actually just another way of saying voltage, and it's measured in volts. So that's a very confusing difference. As an example, we can ask what is the electrical potential energy of the 3 coulomb charge from one side of this plate in the picture to the other, and we can also ask what is the electrical potential experienced by the charge from one side of the plate to the other. These look very similar, but they're actually very different. Electrical potential energy is asking for the work done on the charge. So to calculate that, we can watch the charge move from one side to the other, and we know that the work done is going to be equal to the force times the distance, which is equal to the charge times the field times the distance. So that comes out to be 1,500 joules of work being done by the field on that particular charge. The electrical potential, on the other hand, is the work per charge. So that's going to be the voltage, which is just also equal to the electric field times the distance traveled in the field, which is equal to 500 volts. So very similar sounding questions, but because of that very slight difference in wording, has a very different meaning and answer. Just watch out for that as you're doing these problems involving voltage. This video is about electron volts and how they compare to joules. An electron volt is a unit of energy, just like a joule. It's usually written as EV, lowercase e and capital V. We use electron volts to measure small amounts of energy. So electron volts and joules measure the same thing, but they measure different quantities of that thing. Specifically, 1 electron volt is the exact amount of energy 1 electron or proton gains when it passes through a region of 1 volt of voltage. So that's the definition of 1 electron volt. That's what electron volts are measuring. So it's literally an electron moving through a volt. And when that happens, you get exactly 1 electron volt of energy in the electron. Because voltage is equal to the change in energy over the charge, I can rearrange this equation to find the change in energy. And I know that the charge of an electron is 1.60 times 10 to the negative 19th coulombs. So because 1 electron volt is the energy that 1 electron gains when it passes through 1 volt, 1 electron volt will be equal to 1.6 times 10 to the negative 19th coulombs multiplied by 1 volt. And because that gets me an answer in joules, this allows me to compare electron volts and joules. So again, they're both units of energy, but 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. So this is how you would go from one to the other. You can use this identity to convert from one back to the other. One way that I remember this is 1 electron volt is literally 1 electron's worth of charge, but as a joule instead of a coulomb, because it's just multiplied by 1 volt to get to a joule. To find the number of electron volts electrons gain, all you have to do is multiply the number of electrons by the number of volts, and that's it. So as an example, if 1 electron passed through a region of 1 volt, it would gain 1 electron volt of energy. If an electron passed through a region of 2 volts, again, you just multiply the number of electrons by the number of volts. So here that's 1 electron times 2 volts. So that's going to result in 2 electron volts of energy being gained by the electron. The reason why that happens is that electron passing through that 2 volt space is equivalent to 1 electron passing through a 1 volt region, just like that first example, and gaining 1 volt, and then passing through another 1 volt region and gaining 1 volt again. So I can see that that would gain 2 volts. Similarly, if I had 2 electrons passing through a 1 volt region, they would also gain 2 electron volts. And the reason why that's the case is that those 2 electrons moving through the 1 volt region are equivalent to 2 individual electrons, each moving through their own 1 volt region. That's kind of literally what's happening there. So I know from my very first example that each individual electron would gain 1 electron volt of energy, so altogether they would gain 2 electron volts. So I can use this to understand the fact that the number of electron volts gained by electrons is equal to the number of electrons multiplied by the voltage. So now I'm ready to do some example problems with what I've learned. Problem 1 says how many joules are in 250 electron volts. So this first one's pretty simple. We just have to convert from electron volts to joules. So I'll use a factor label where I want to get rid of electron volts. So I'll put that in the denominator. I'll put joules in the numerator, and then I'll write numbers next to them to make the numerator and denominator equal to each other. If you're confused about converting units, I've left a video on using this method to convert units in the video description. When I multiply this fraction out, I get 4.0 times 10 to the negative 17th joules, so that's how many joules there are in 250 electron volts. Problem number 2 says how many electron volts are in 2.6 times 10 to the negative 8th joules. So I just take that number, I multiply it by a conversion factor. Here I have joules in the denominator because I'm trying to get rid of joules and replace it with electron volts. And when I do that, this is the answer that I get, 1.63 times 10 to the 11th electron volts. Problem number 3 says 25 electrons pass through 5 volts. How much energy do they gain in electron volts? So the number of electron volts gained is just the number of electrons multiplied by the number of volts. So that's going to be equal to 125 electron volts. Problem number 4 says 30 protons pass through 8 volts. How much energy do they gain in joules? Now, I know that protons have the same magnitude of charge as electrons, so they're also going to gain that same amount of energy. It's just 30 protons, the number of protons times the number of volts. So that's going to be 240 electron volts, but I want that in joules, so I just have to use my method for converting from electron volts to joules. And when I do that, I find 3.84 times 10 to the negative 17th joules is how much energy those protons gained. Problem number 5 says electrons gain 40 electron volts. After passing through 8 volts, how many electrons are there? So I know that the number of electron volts is equal to the number of electrons times the voltage. So if I rearrange that equation, I find that the number of electrons, if I divide both sides by voltage, is equal to the number of electron volts over the voltage. So I just plug in my numbers that I'm given, and I find that the number of electrons is 5. Problem number 6 says electrons gain 6.72 times 10 to the negative 18th joules after passing through 7 volts. How many electrons are there? So here I'm going to use the same equation as problem number 5 because I'm trying to find the number of electrons, but I don't have the number of electron volts. I have joules instead, so I'm going to have to convert joules to electron volts. So I'll multiply that by 1 electron volt over 1.6 times 10 to the negative 19th joules. And when I do that, I find that I have 42 electron volts. So I plug in my number, I also plug in the 7 volts to find 6 electrons. So that's what electron volts are, they're just another unit of energy, and that's how you identify their number and use them to solve other problems. This video is about resistance and resistivity. These are the definitions of each. I'm going to go through both with a quick example for each. First of all is resistance. Resistance is the amount of opposition current will experience to its flow when moving through an object. So it's the resistance that an object puts on current. It can be thought of as the amount of voltage lost per current moving through the material. So if you have some current moving through a certain material, it's going to take some energy to move through that material, and the more energy it takes away from the current, the more resistance that material has. The variable for resistance is capital R, and the unit is capital omega, which we pronounce as ohm. It's named after a physicist who worked a lot with current. And the equation for resistance is equal to the voltage drop across a material divided by the current that's experiencing that voltage drop. As an example, we could say a current of 5 amps drops by 4 volts of electric potential as it moves through a resistance, and we want to know the value of the resistance. So these are the numbers I'm given by that problem. And I'm going to imagine that, again, this current is moving through this material and it drops by 4 volts. And so as a result, I can see that the resistance here is 4 volts over 5 amps, which means that it is 0.8 ohms. That's how we would say that. Resistivity is the amount of resistance a given cross-sectional area of a material will experience per unit of length of the material. So the variable for this is rho, it's a Greek symbol, and the units are ohms meters. I'll explain why in just a moment. And the equation is resistivity is equal to the resistance multiplied by the cross-sectional area of the material divided by the length of the material. So the reason why this unit works, you can see on the bottom there, that if I just plug in the units for each variable, they cancel out and become ohm meters. Just to build your intuition here, resistivity is the amount of difficulty that current will experience per part of the material, per length and per area. So if I rearrange this equation for capital R to see how much resistance current will experience, I can see that the equation kind of makes sense. I can see that R is going to be bigger if there's more resistivity. So if there's more resistivity, there's more resistance. And it's also going to be bigger if there's more length of the material. And it's actually going to be smaller if the area of the material gets bigger because that area is in the denominator. So I kind of think about this like a current of water moving through a pipe, where if there's a smaller area of the pipe, that's going to be more difficult for the water to move through than if there's a bigger area. So a smaller cross-sectional area is going to lead to more resistance and more difficulty for the current to move through. And if the pipe is longer rather than shorter, that means that the current is going to experience more resistance because it's just going to take longer to get through. So that's a quick explanation of why that equation works in that way. We can do an example problem with this equation. What is the resistance of a piece of copper wire where the resistivity of copper is 1.68 times 10 to the negative 8 ohms meters with a diameter of 6 millimeters and a length of 4 meters? So I need to figure out the cross-sectional area before I solve this problem, and the area is going to be equal to pi r squared because that cross-section is a circle, and r is going to be half the diameter, the radius is half the diameter, so that's going to be 3 millimeters or 0.003 meters. It's important to always convert back to your base unit of meters. Multiplying that by pi gets me 2.8 times 10 to the negative 5th meters squared. And because the resistivity is this number, I can plug this in with the length of 4 meters, and I'm trying to find R, so I just plug this into that rearranged equation for R, and I get a resistance of 0.0024 ohms. And we'd expect that to be small because copper wire is material that we use to allow electricity to flow. So we would expect us to want a very small resistance for that material. And that's what you have to know about resistance and resistivity. This video is going to be about circuits and the basic notation we use to describe them. A circuit is a path along which an electrical current can be carried. That's the definition. So if we say circuits, that's what we are talking about. I'm going to have you take a moment to copy down these definitions. Just pause the video because these are very in-depth, but these are the basic building blocks of a circuit. Specifically, batteries, wires, and resistors are what we're going to be worried about in this video. So a common misconception students have coming into class is that batteries give electrons to a circuit. You may remember that current is actually the movement of electrons, and what students imagine happening is that there's no electrons in a circuit or just the natural electrons of the metal, but all the electrons in the current come from the battery. Like the battery contains the electrons, and when it's plugged into a circuit, the electrons are moving around the circuit in a current. But what actually happens is that electrons already exist in the metallic material that makes up the circuit, and the battery just pushes the electrons that are already in the wire along the circuit. So as an example here, I have an incomplete circuit. It has a hole in it, and so the electrons can't move right now. But when I introduce a battery, the battery begins to push the electrons around. It gives the electrons voltage, potential energy, and they begin to move around the circuit like this. So that's a common misconception to watch out for. And if I remove the battery, you can see that the electrons stop moving. So the reason why the battery is able to push electrons is that the electrons are repulsed from each other. The battery provides a voltage that adds energy to the electrons, which allows them to push the electrons in front of them. If this path of electrons being pushed by the voltage continues all the way back to the same voltage source, this pattern continues and the voltage can keep electrons moving around the circuit. So by the time they get back to the battery, there's no more electrical potential, but when they move across the voltage, there's lots of electrical potential. So the battery is basically the thing that's pushing them along. It's accelerating the electrons inside of itself to push other electrons forward. For the circuit to work, there needs to be a path all the way from one end of the battery back to the other. If that path is broken, all the electrons stop moving and the circuit does not work. We call circuits that have a complete path back to the battery closed circuits, and circuits without paths back to the battery open circuits. So basically, the air between the wires kind of provides a wall in an open circuit that electrons can't pass through. There's just too much resistance for them to move through it. And just remember, the direction of conventional current is the opposite of the actual direction of the electrons. From now on, I'm going to be using these arrows to show the direction of the conventional current. So even though the electrons here are moving counterclockwise, the conventional current points in the direction that these imaginary positive charges would move. It points in the opposite direction of the real flow of the electrons. Conventional current flows away from the positive end of the battery and toward the negative end. Just remember that that larger side is considered to be positive and the smaller side is considered to be negative. And of course, what's actually happening here is that the electrons are actually attracted to the positive end and repulsed from the negative end. So the electrons are actually going the other way around the circuit. But because this shows the conventional current, it goes from positive to negative. If there's more than one path back to the battery, the current will split in two and take both paths. We'll learn how to find the exact amount of current that follows each path later in this unit. So what would happen in this circuit is that current would come out of the positive end, and this is the total current moving in the circuit, and right here it would split into two smaller currents. We can call this I2 and I1. And they'll continue to go, but those two together will add up to the total current. It's kind of like a split in a river, which we'll talk about later. So I1 plus I2 will equal the total current. And again, what's happening here is that the electrons are actually just splitting up and moving in different directions. So before that had a total charge of 2 electrons, and now in this particular case, each individual current has a charge of 1 electron moving through it. So those currents can continue until they meet up again and connect back into a single overall current. So right here, it would become a total overall current again. So those individual currents add together to make the total current moving through the battery. If a split in the circuit does not lead back to the battery, no current will flow into that split. And this is not because there aren't electrons in that part of the circuit, it's because the electrons in that part cannot be pushed through the resistance in the open part of the path. So what's actually happening here is that the electrons just can't be pushed through that one path, so the only place they flow is in that closed part of the circuit. Circuits always include at least one resistor. In a resistor, the electrons lose some of the energy that they're gaining from the battery in the process of pushing through the resistance. The total voltage lost by the current in the circuit is equal to the voltage added by the battery. So every time the current moves through a resistor, it's going to lose some voltage. It's going to lose some electric potential. And the total that it loses in all the resistors together will be equal to the total voltage gained by the battery. So any energy that the battery gives the electrons is going to be lost in the resistors, and then the process kind of repeats. The electrons with no energy go back to the voltage source, and the process repeats itself. So here, because this is a current going through resistor 1, I would label this voltage drop 1. It's losing that much voltage as it moves through that resistor. To explain this, I'm going to use an analogy that I came up with that I'm going to call the water analogy, where I'm going to compare this circuit to water moving around a machine. So I'm going to imagine that this water moving in this machine is similar to the circuit, and I'm going to use this analogy to explain why they are similar to each other. So I know that there's current flowing all around the circuit, which is one reason why I'm using the water analogy, because we also use the word current to describe water. And the battery is adding potential to the electrons. It's adding electric potential or voltage to the electrons. So the total amount that the battery adds is equal to the total electric potential that the electrons will have. And right after leaving the machine, in this case the battery, the current has the maximum electrical potential that it will have, the maximum voltage that it will have. In the same way, I can imagine that there's current flowing all around here as water, and at this point right here, I'm imagining that some machine is physically raising the water so that we can do work with it later. So at that one point, a machine is physically raising water to the top of this machine. And I can see that this total height is going to be kind of equivalent to the total potential that the water gains as it's being lifted by this machine. And right after leaving the machine, the current has the maximum potential. In this case, that potential is gravitational potential. And I can see that, yeah, this is where the water has the most potential because it's raised that entire height. It's just left the machine that raises it higher. So just like we have this machine raising water, the battery kind of raises the electric potential of the electrons. And right after they leave the battery, they're at some maximum electric potential. So what happens next is that the current uses some of its potential to move through a resistance. So we can say that it drops by V1 here, V2 here, and V3 here. So those are three different potentials that it lost in each resistor. And altogether, the total voltage is going to be equal to the sum of those three potentials. And here, right after it goes through all the resistors in the circuit, the current has lost all its potential. It's still being pushed by the current before it back to the machine to give it more potential. So in the same way, after gaining all that height, we can imagine that this water drops some of its potential to turn these machines. I'm not sure what they're doing. I'm just imagining that in order to make them turn, the water has to be moving with some velocity that it gains by falling a certain amount. So the water is losing some of its potential to make these machines work. And you can see that if you add up all three of those heights, all three of the potentials that are lost to those machines, those three potentials added together will be equal to the total potential added by the battery. So that's kind of what's happening here. The battery adds potential and each resistor takes away potential until there's none left at the bottom. So here the current has lost all its potential. It's still being pushed by the current before it back to the machine to give it more potential and start the process again. So that's the basics of how a circuit works. In a circuit, a battery provides electric potential or voltage, current moves through the circuit with that potential, and it loses that potential as it goes through each resistor, doing some work in the resistor until it has no potential left, and it comes back to the battery to be given that same amount of potential again, and that process repeats. So we're going to be doing a lot with circuits, but that's the basic physical idea of what's actually going on inside of them. This video is going to be about series and parallel arrangements of resistors and equivalent resistance, which together are kind of the centerpiece of this unit. They're probably the single most important idea. Both series and parallel are names for paths that current can take through resistors. Resistors are said to be in series if current that passes through one needs to pass through the other as well. So just remember from the last video that current is being pushed by other electrons, so it can't really move backwards. So what that means is that if this electron passes through this first resistor R1, there's no way it can turn back and go back through R1. To continue, it's also going to have to go through R2. So what that means is that if it goes through R1, it also has to pass through R2 as well. So we would say that R1 and R2 are in series. In comparison, resistors are said to be in parallel if current that passes through one cannot pass through the others. So resistors 3 and 4 are in parallel with each other, and I'll show you why. We can imagine an electron starting at one end and taking one path through this arrangement, like this. So in this case, it passed through R3 and not through R4. We can also imagine it passing through R4 and not through R3. However, if we imagine it trying to go through both like this, it's going to hit a dead end over here. Because this isn't actually just one electron, there are other electrons following this path, it's going to hit a dead end, and so these electrons wouldn't actually be able to continue in this way because there are already electrons moving through another part of the circuit. So because of this, current that passes through R4 cannot pass through R3 and vice versa. So this is not possible, so we would say that R3 and R4 are in parallel with each other. There are important rules for current and voltage and resistance in series and parallel arrangements. Starting with current, in a series circuit, the current going through each resistor is equal to the total current, whereas in a parallel circuit, the sum of the current going through each resistor is equal to the total current. So if I were to draw a picture of what these currents are doing in the series circuit, it's just one current consistently moving through all of them. It's just one total current. Whereas in the parallel circuit, the total current is going to break up into two smaller currents that go through resistor 1 and resistor 2, and then come back together and form a total after. So the total current is going to be equal to the first current plus the second. This makes sense if we use the water analogy. I can see here that these two resistors in the water analogy are arranged in series on the left and parallel on the right. I can see in the series arrangement that the total current, the total amount of water, has to travel through both resistors. Whereas in the parallel circuit, the current has to split into two smaller currents, go through each resistor, and then come back together after. So that's why those two current rules work for series and parallel. The rule for voltage in series and parallel works like this. In series, the sum of the voltage drops across each resistor is equal to the total voltage drop in the circuit. So if this is the total voltage drop, if there's a total drop from R1 to R2, then that total is going to be equal to the sum of the voltage drop across R1 and the sum of the voltage drop across R2. In comparison, in a parallel circuit, the voltage in each resistor is equal to the total voltage. So if there's a total voltage drop here, that's going to be equal to voltage 1, and it's also equal to voltage 2. Again, we can explain this with the water analogy, because if we consider the voltage to be kind of like the height of the water, I can see that in the series circuit, the total height dropped on each resistor added together, H1 plus H2, is going to be equal to that total height. So the total potential lost in each resistor added together makes the total potential. Whereas in a parallel circuit, the total height gained will be equal to the total height dropped in each resistor. So the voltage is equal in a parallel circuit. I now need to define equivalent resistance, which is really just a fancy way of saying total resistance. Equivalent resistance is specifically talking about the resistance that multiple resistors provide. In other words, it means finding a single resistor that is equivalent to the multiple resistors in a circuit. In a series circuit, the equivalent resistance is equal to the sum of the individual resistors, or the sum of their individual resistances. That part's pretty simple. However, the parallel rule is pretty tricky. In a parallel circuit, the inverse of the equivalent or total resistance is equal to the sum of the inverse of the individual resistances. That equation looks like this on the right. I'm going to give you some examples of using those. I'm going to find the equivalent resistance for the following circuits. I can see number one is a series circuit, which means that I'm just going to add the resistances together like this. So I get a final resistance of 8 ohms. So that means that these two resistors, if you put these two resistors into this shape in your circuit, it's basically the same as putting a single resistor in with a resistance of 8 ohms. And I can see that in number 2, those are also a series arrangement. So I'm just going to add them together to find their equivalent resistance. And that's equal to 12 ohms. So these 3 resistors behave like a single 12 ohm resistor. I can see that in number 3, these resistors are parallel to each other, so I'm going to need to use the rule for parallel resistances. I'm going to plug them in like this, and the first step of solving these problems after plugging them in is finding a common denominator, so I can see that that's going to be 10 ohms. So when I combine these, this is going to be 3 over 10 ohms is equal to 1 over the equivalent resistance. A very common mistake is for students to either stop here or to just add the denominators together. So this is definitely not 2 over 15, it's definitely not 1 over 15, it's 3 over 10 ohms is equal to 1 over the equivalent resistance. Taking the inverse of both sides, I get that the equivalent resistance by itself is equal to 10 ohms over 3, which is equal to 3.3 ohms. So those two resistors behave like a single resistor of 3.3 ohms of resistance. So a pattern you might have noticed is that in series, the total resistance is greater than the individual resistances, whereas in parallel, that total resistance is actually less than the individual resistances. So it actually becomes easier to go through resistances if you put them in parallel. In number 4, I'm just going to plug those 3 into my equation, solve it out using some math, and when I solve that, I get an equivalent resistance of 1.7 ohms. So that would be the equivalent resistance in number 4. A complex circuit is a circuit with a combination of series and parallel arrangements. To simplify a complex circuit, find arrangements inside of it that are simple series or parallel circuits, simplify them to a single resistor, and repeat until the entire circuit is one resistor. So this is a very complex circuit, but even this can be pretty easily broken down if we just step back from it and just focus on simple pairs of resistors or simple sets of resistors that are in simple series or parallel arrangements with each other, and begin to break them down. As an example, I can see that these are in parallel with each other, so I can use the parallel rule to find their equivalent resistance. And when I do that, I find the equivalent resistance is 3 ohms. So these two behave like a single resistor of 3 ohms, like this. Now I can look for other simple arrangements. I can see that this is a simple series arrangement now, so I plug that into my series equation and I get 5 ohms as the equivalent resistance. So these two behave like a single resistor of 5 ohms. I'm going to do the same thing up here and say that this is 9 ohms because this is another simple series arrangement. And now I can see that these two are in a simple parallel arrangement with each other. Plugging that into the parallel rule, I get 3.2 ohms of equivalent resistance. I rounded there a little bit. And finally, I can see that these two resistors are in a simple series arrangement with each other. So adding those together gets me 8.2 ohms. So I just simplified that circuit. All of those resistors together behave like an individual resistor of 8.2 ohms. So that one resistor is the equivalent resistance of that complex circuit. All those resistors working together behave just like an individual resistor of 8.2 ohms. So that's how you find the equivalent resistance using series and parallel. In the next few videos, we're going to learn how to get more information out of that. This video is about Ohm's law. V is equal to IR, and the title kind of explains the whole video. Ohm's law tells us that voltage is current multiplied by resistance. This is really just a rearrangement of that equation you learned in the resistance video. I'm just going to run through and show you a few simple examples of Ohm's law and then a more complex example. So Ohm's law can be used to find either voltage, current, or resistance. So you can see that for each of these, we have two of the three things that we need to understand what's missing. So for all three of these, we can just use V equals IR, rearrange them to find the variable that we're looking for, plug in the numbers that we're given, and find the answer. So in this first example on the left, that current experiences a voltage drop of 12. In the middle example, the current moving in the circuit is 0.5 amps. And in the last example, the resistance in that resistor is 33.3 ohms. Ohm's law can be used to find either individual currents, voltages, and resistances, or the total current, voltage, and resistance given the other two. As long as each variable applies to the same object in the circuit, or all three apply to the total circuit, the equation works. So V1, the voltage drop in resistor 1, will be equal to the current in resistor 1 times the resistance of resistor 1. Voltage drop 2 will be equal to the current in resistor 2 times the resistance of resistor 2, and the total voltage will be equal to the total current times the equivalent resistance. So just plugging this in, I'm going to say that I have a current of 2 amps moving around the circuit. So applying V equals IR to each resistor gets me a total voltage of 10 across the first resistor and a voltage of 6 across the second resistor. And I can see here that each equation holds true. The current going through the first resistor of 5 times the resistance is equal to 10. So we can see that Ohm's law here holds true for both the individual resistors and the total resistance, because the total resistance here is 8 and the total voltage is 16. So 16 is equal to 2 amps times the equivalent resistance of 8 also holds true. So this is how we use Ohm's law to find the voltage, current, and resistance in each resistor and in the total circuit. Okay, this is a very short video on ohmic versus non-ohmic resistors. Ohmic resistors are any resistors that obey Ohm's law, V equals IR, and any increase in voltage creates a linear increase in the current, so that's pretty straightforward. And if you look at V equals IR and rearrange it so that I is equal to 1 over R times V, you can see that if V is our X value and I is our Y value, 1 over R is taking the place of the slope in that equation, so the slope of this line would be 1 over R, the resistance of that specific resistor. In comparison, non-ohmic resistors are resistors that do not obey Ohm's law. Any increase in voltage creates a nonlinear increase in the current, so the resistance of the material changes based on the current moving through it. So in this case, you can see that the more voltage you apply, there's a greater magnitude of current going through, and it's increasing in a nonlinear way. So that means that more current is going through and experiencing less of a voltage drop per current than before. So that would actually mean that in this case, the resistance is going down over time. Which makes sense, because if the slope at any one point is 1 over R, and the slope is increasing, that means that R must be decreasing as it goes. This video is about ammeters and voltmeters, two measurement devices we use in circuits. These are the symbols for ammeters and voltmeters. Ammeters measure the current in a wire, so literally they're like amp meters. They must always be placed in series with the location being measured. I'll explain why in just a moment. And an ideal ammeter has a resistance of 0 ohms, because any resistance would change the current being measured. So again, I'll do some examples of that in a moment. A voltmeter measures the voltage in a wire, and voltmeters must always be placed in parallel with the location being measured. Again, I'll explain why in just a moment. An ideal voltmeter has a resistance of infinity ohms. It has an infinite resistance because it needs to stop any current from moving through it and taking away from what it's measuring. So just as an example, I can see here that using V equals IR and the equivalent resistance of the circuit is 5, that the total current moving through the circuit is 2 amps. So if I were to place an object to measure the current, I need the current going through that measurement device to be the same as the rest of the circuit, so I would place it in series with the rest of the circuit, because the rule is that in series, the current stays the same for all objects, so that 2 amps is also going through that ammeter. And because this is 0 ohms, the total equivalent resistance of the circuit is still 5, which means that the total current is still 2. So if we keep this at 0 ohms, it's not going to affect the current at all. So we would say the ammeter reads 2 amps. So we would know that 100% because we know that 2 amps are flowing through the region where the ammeter is placed. We call an ammeter with 0 ohms an ideal ammeter, so this is an example of an ideal ammeter. We put it into the circuit without it affecting our measurements at all, so because it perfectly measures the circuit itself without affecting the results, we say that it's an ideal ammeter. So 0 ohms of resistance means an ideal ammeter. Now let's imagine that we place an ammeter down that does not have a resistance of 0. Let's say it has a resistance of 5 ohms as an example. I can see now that the equivalent resistance of the circuit is 10, 2 plus 3 plus 5, because the ammeter is in series with the other resistors. So that's going to mean that the current is now 1 amp, because V equals IR. So 10 volts divided by 10 ohms of resistance is equal to 1 amp of current. So this ammeter is now changing the current that it's supposed to measure, which is bad. We do not want our measurement devices to change what we're trying to measure. So this is an example of a non-ideal ammeter. This is something that's changing the results, and unfortunately in the real world, all ammeters are non-ideal to some extent. Most of them have very low resistances and we can get very close results, but there's no true ideal ammeters. Now we can add a voltmeter and measure the voltage with it. So I'm going to imagine that we're measuring the voltage across this 3 ohm resistor. So to do that, according to our rule, we need to put the voltmeter in parallel with the part of the circuit that we want to measure the voltage of. So here I want to know how much the voltage drops as the current crosses the 3 ohm resistor, so I put that voltmeter in parallel with the 3 ohm resistor. So I'm going to take a moment to show you why it is that we place that in parallel and why it is that we need that voltmeter to have an infinite resistance. So I'm going to show you both right now. So to build up your intuition on this, we don't want any current moving through that voltmeter. Ideally, the voltmeter wouldn't be affecting how much current is moving through the 3 ohm resistor. It wouldn't be taking any for itself. It's just leaving the current to move through the 3 ohm resistor. So if that voltmeter has an infinite resistance, and resistance is the voltage drop over the current, that means that infinity is equal to the voltage over the current, and that basically leaves two options. Either the voltage is equal to infinity, or I is equal to 0, because as a denominator approaches 0, the value approaches infinity. And we know that the battery isn't giving infinite voltage to this circuit, so the only other option is that the current in the voltmeter specifically is 0. So if we make that resistance infinite, no current will pass through the voltmeter, leaving the current in the circuit unaffected. I can also show that the equivalent resistance for that parallel part of the circuit, because 1 over infinity is the same as 0, is just going to be 3 ohms. So because the resistance of the voltmeter is infinite, the equivalent resistance of that parallel part of the circuit is just the same as if the voltmeter weren't even there, if it were just the 3 ohm resistor. So this is good. We want ideal ammeters and voltmeters to basically behave as if they're not there. They're just measuring what's already present without affecting it at all. So this is the reason why we want an infinite resistance on voltmeters. So because the total resistance in the whole circuit is still 5 ohms and the voltage is 10, the current is still 2, and because no current is going through the voltmeter itself, all that current is going through the 3 ohm resistor. So I can see that the voltage drop is 6 in the 3 ohm resistor using V equals IR. And because the voltage is the same for all paths in parallel, that means that the voltmeter is also experiencing a 6 volt drop. So because that's moving through the voltmeter as well, the voltmeter can detect that, and that's how we read the voltage drop on the 3 ohm resistor, by putting the voltmeter with infinite resistance in parallel with it. So we would say the voltmeter reads 6 volts, and this is an ideal voltmeter because it is not affecting the voltage drop of the circuit. We can measure any region that we want with a voltmeter. For example, we could put it like this, and in this case, we're measuring the voltage drop across both the 2 ohm and the 3 ohm resistor. And again, we're giving this infinite resistance. And so this is still a 2 amp current, and so therefore the voltages are still 4 and 6, so altogether the total voltage here is 10. And you can also prove that that's 10 by saying, oh, well, those two resistors are in series, so they add up to 10, and the total resistance on one side of a parallel circuit is the same as the other, so in the voltmeter, that total voltage in the voltmeter must equal the voltages in the other side, so when you add those together, you get 10. So again, the voltmeter is just measuring that total voltage drop across that region. So here we would say the voltmeter reads 10 volts. If we put it over here, there's no voltage drop. All the voltage is happening here in the resistors. So because there's no voltage drop there, if we put the voltmeter there, that would just read 0 volts. Now let's look at a non-ideal voltmeter. I'm going to give this voltmeter a very high resistance, but not an infinite resistance. So this is 1 kilo ohm or 1000 ohms. If I plug this into my equivalent resistance equation,
I can see that the equivalent resistance of that part of the circuit is going to be 2.99 ohms, so very close to 3 ohms, but not quite. Because the voltmeter is not ideal, it is ever so slightly decreasing the resistance of that part of the circuit. So when I add this to the 2 ohm resistor and then use V equals IR, I find that the current moving through the circuit is 2.004 amps, which is just a little bit too big. It's just a little bit bigger than what we had before. So I can see that the voltage drop in that first resistor is going to be 4.008 volts. So that means that because the total voltage is 10 and it dropped 4.008 volts, the second voltage drop across that parallel arrangement is going to be 5.992 volts here and here. So the voltmeter ever so slightly changed the voltage that it was trying to measure because it didn't have an infinite resistance. So we would say that this is a non-ideal voltmeter. Any voltmeter with a non-infinite resistance is non-ideal. There are going to be specific problems that ask you where you should place voltmeters and ammeters to measure the voltage and current in different resistors. So just as an example, I'm just going to throw a bunch on this circuit and tell you what each one is measuring. So this one can measure the voltage drop across resistor 1. This one measures the voltage in resistor 2, resistor 3, resistor 4. We can also measure across both resistor 2 and resistor 3, or across the whole parallel arrangement like that, or even across all the resistors in the circuit together. For the ammeters, this ammeter can measure the current moving through resistor 1, which you can see is also the total current in the circuit. If we placed it right here, it would measure the current in resistor 4, and if we placed it right here, it would measure the current in resistors 2 and 3.
This video is going to be about power in electrical circuits. So we remember from last year that power is work divided by time, or the change in energy divided by time. And if I multiply this out, I can just put a Q in the numerator and denominator like this because they cancel each other out. And remembering that Q stands for electrical charge, I get that power is equal to charge divided by time multiplied by the work done divided by the charge, which you may notice is actually equal to the current multiplied by the voltage. So we can have a new equation for power in an electrical circuit, which is that current times voltage is equal to the electrical power. Notice this is still the power that we were dealing with last year, the work done per time, the change in energy per time. We're just finding it in circuits now. So using V equals IR, I can prove that power equals IV means that power is also equal to I squared times R, and it's also equal to V squared over R. So those are three equations for power. I'll do some example problems. This is example 1. What is the total power dissipated in this circuit, and how much energy is dissipated in the circuit in 1 hour? So just writing down what I know. I can use the three resistances to find the total equivalent resistance, which is 15 ohms. Plugging this into V equals IR gets me a total current of 2 amps moving through the circuit. And I know that in a series circuit, the current is the same everywhere. So that means that for each resistor, that resistor is getting 2 amps of current. So to find the power in each resistor, I can use I squared times R. Plugging in my numbers gets me a power of 20 watts in the first resistor, 32 watts in the second resistor, and 8 watts in the third resistor. And so the total power is just going to be the sum of those. Whenever you're finding the total power, it's always just the sum of the power in each resistor. So the total power here is 60 watts. And to know how much energy is dissipated in the circuit in 1 hour, we can use the fact that power is equal to energy over time, or power times time is equal to energy. And so this means that we can just multiply the power times 3,600 seconds in 1 hour to get the change in energy, which here is equal to 216,000 joules. That's how much energy the circuit would dissipate in 1 hour. Example 2 has the same three resistors arranged in parallel instead of series. Example 2 uses the same three resistors, so they each have the same resistances as example 1, but here they're arranged in series instead of parallel. And I remember that my rule for series is that the total voltage in series is equal to the voltage in each individual resistor. So there is a 30 volt drop across each individual resistor. I can use these values for voltage along with the resistances to find the current and then find the power. So I'll start by finding the current using V equals IR. Because this is a parallel circuit, it's possible for the current to be different across each individual resistor. And that's what I find. I can then use the current in P equals IV to find the power dissipated in each resistor. And these are the powers that I get when I do that calculation. To find the total power in the circuit, I just have to add the power dissipated in each individual resistor. And when I add those three numbers together, I get 743 watts. So that's the total power dissipated in this circuit.
You may notice that these are the same three resistors, but they're producing much more power in this circuit than they were in the series circuit. And this is actually going to be a pattern that holds for all circuits with the same resistors. If you use the same set of resistors, a parallel arrangement will produce more power than a series arrangement. So the reason why this is true is that both of these have the same total voltage, but in the series arrangement, that voltage is being split up into each of the three resistors, whereas in the parallel arrangement, each resistor gets the total voltage. So if that total voltage is bigger for each resistor, you can see that because P equals V squared over R, a bigger voltage in the same resistance will result in a much bigger power. So that's why parallel circuits will always have more power than their equivalent series circuits. So this will hold true. The more of these resistors that you have in parallel with each other, the more power will be produced. This is an important pattern to know, and that was what you had to know about finding power in electrical circuits. This video is about internal resistance. Internal resistance refers to the resistance inside of a battery. No battery is ideal, and all contain at least a little resistance inside of them. In IB, we use this symbol to show internal resistance. So we've got this battery. This dotted line represents the kind of barrier of the battery. Anything inside of that dotted line is inside of the battery, which we symbolize with those cell symbols, and it also contains an internal resistance, which we symbolize just like any other resistor with that resistor symbol with the lowercase r. We call the voltage that the battery delivers to the rest of the circuit the terminal voltage. So we'll talk about that more in just a moment. And the variable for internal resistance is lowercase r. So before this, we were using capital R for resistances. For internal resistance specifically, we use lowercase r. In all previous problems, the voltage we've been talking about has really been the terminal voltage of the battery, just the voltage that the battery gives to the rest of the circuit, excluding the voltage drop that occurs within the battery itself. Here's an example problem with internal resistance. What is the terminal voltage of this battery? So we can see that this battery contains this voltage of 10, and the internal resistance is 2 ohms, and it also has a 5 and 3 ohm resistor outside of the battery. So I can see that the equivalent resistance in the circuit is going to be equal to 10 ohms, because the internal resistance behaves like any other resistor in the circuit. It just happens to be inside the battery. So it's also in series with those 2 other resistors, so those add together to make 10 ohms. Using V equals IR, I can see that the current in this circuit is 1 amp. So if this current is 1 amp, each of these resistors is experiencing 1 amp of current. And I can use that to calculate the voltage drop in each resistor. So in the 3 ohm resistor, there's a voltage drop of 3, and in the 5 ohm resistor, there's a voltage drop of 5, using V equals IR. And inside of the battery, there's a voltage drop of 2. So what that means is that if we just pay attention to what's happening outside of the battery is delivering 8 volts to the outside of the circuit. So we would say that the terminal voltage of this battery is 8 volts. From one terminal of the battery to the other, it delivers 8 volts. There's an 8 volt drop in electrical potential. In internal resistance problems, we refer to the voltage source inside the battery as the electromotive force, or EMF. This can be confusing because EMF is actually not a force, it's a voltage causing electrons to move. It's measured in volts and can be used as the voltage in the circuit when you are considering the internal resistance. So when we say EMF, we mean that full total voltage inside of the battery, whereas when we just use the word voltage, we're usually really referring to the terminal voltage. So there's a difference here. EMF refers to the total voltage experienced by everything in the circuit, including the internal resistance, whereas voltage is referring to the terminal voltage, just the voltage drop that's delivered outside of the battery. The IB symbol for EMF is epsilon. That's a lowercase epsilon specifically. It's a Greek letter. So we would say in this problem here that the EMF epsilon is equal to 10 volts, but the voltage, or the terminal voltage, is equal to 8 volts. So that's the difference between these two things. So going back to this problem here, I know that the current flowing through this is 1 amp, so that means that the voltage drop inside of this battery is 2 volts. So I can see here that the EMF is going to be equal to that voltage drop inside of the battery plus the terminal voltage of the battery. So basically, whatever voltage drop happens outside of the battery plus whatever voltage drop happens inside the battery, IR, those two things added together are equal to the EMF of the battery. So in this case, the outer voltage drop is 8 and the inner voltage drop is 2, so altogether the EMF is clearly 10 volts. If I rearrange this equation and call V the current times the equivalent resistance outside of the battery, I end up with this equation. The EMF is equal to the current multiplied by the sum of the resistance in the circuit plus the internal resistance of the battery. This equation appears in your IB data booklet. So this is the information that you're given in your data booklet about EMF and internal resistance in general.
Going back to this first equation, if I rearrange this equation to look like this, and then create a graph of the voltage in the circuit on the y-axis and the current in the circuit on the x-axis, I can see that this equation fits y equals mx plus b, where m is the slope and b is the y-intercept. So this is going to yield an important pattern that's going to show up on a few different IB problems, where if you make a graph of the voltage on the y-axis and the current on the x-axis of a circuit with internal resistance, the y-intercept of the graph is going to be the EMF of the battery, and the slope of the graph is going to be the negative internal resistance of the battery. So if you're ever asked a question about which graph shows a greater internal resistance, it's going to be the one with a steeper slope, and the one with a greater EMF is going to be the one with a greater y-intercept. So basically, using a voltage current graph, you can find the EMF using the y-intercept and the internal resistance using the slope. This lecture is going to be about simple harmonic motion, which has a very precise definition that's going to be important to understand. The definition is periodic motion around a central point of equilibrium where there is no net force. There is a restoring force that acts in the opposite direction proportional to the displacement from the equilibrium position and acts in a direction opposite to that displacement. So that definition is pretty advanced. I'm going to take you through it one step at a time. Two of the most common objects that occur in simple harmonic motion are the spring and pendulum. And both of these have what's called an equilibrium position. And at the equilibrium position, there is no net force. That's one of the definitions of simple harmonic motion. There has to be a certain point where there's no net force on the object from the system. So you can see there are different reasons for why this is the case. With the spring, that's just the spring's natural length, so it doesn't put a push or a pull on the orange box. And on the pendulum, at that exact point, the force of gravity is being perfectly balanced out by the force of tension, so there's no net force at that point either. So this is the first big idea of simple harmonic motion. Any object in simple harmonic motion goes back and forth around an equilibrium position where there's no net force. So these objects are going to get farther away from and then closer to that equilibrium position as they move back and forth. So as the spring is displaced farther away from its equilibrium position, you can see that there is a bigger and bigger spring force pulling the object back toward the equilibrium position. So the farther away you go from the equilibrium position, the more the spring tries to push or pull you back to that equilibrium position. In a previous video on elastic potential energy, I talked about Hooke's law. I'm going to bring that up again here, and I'll link that other video in the description of this video. So when we're describing a spring, delta x is the displacement of the spring from its equilibrium position. Fs is the force applied by the spring on the object. And in that Hooke's law equation that you can see at the bottom, the spring force is equal to the spring constant times x. And that's negative just because the force always points in the opposite direction as the displacement from the equilibrium position. In the picture in the slide, you can see that the displacement is to the right, but the force is pulling it back left. That makes sense. However you displace the spring, it's going to pull opposite to that displacement. So looking back up at my definition of simple harmonic motion, the definition says that there is a restoring force that acts on the object that is linearly proportional to the displacement from the equilibrium position and acts in a direction opposite to that displacement. So here I can see that Fs is playing that role. It gets bigger as the displacement from the equilibrium position gets bigger, and it pushes back toward the equilibrium position in the opposite direction of the displacement. And Hooke's law is linear because it obeys the form y equals mx plus b. You can see that it fits that form. So if you were to graph that on a linear graph, negative k would be your slope and 0 would be your y-intercept. So a spring fits the definition of simple harmonic motion. There's this restoring force that gets bigger in a linear way compared to the displacement. There's a linear relationship between the force that pulls the object back and the displacement away from the equilibrium position. So we're now going to look at the pendulum. So the pendulum's displacement occurs at a certain angle from the equilibrium position like this, and the farther away from the equilibrium position it gets, the more unbalanced the force of gravity on the pendulum will be. I'm going to show you why using this animation. So you can see that there's a force of gravity going straight down on this pendulum. And if I split this up into an x and y component along the angle of the pendulum,
I can see that this component is going to be the force of gravity times sine of the angle of the pendulum. And the other force, the other component, is pointing in a parallel direction to the tension of the rope of the pendulum. And because the pendulum isn't falling up or down in that particular green direction, that means that the forces are being balanced out. So both of these must be Fg times cosine of the angle of the pendulum. So because those are being balanced out, the only net force on this pendulum is Fg sine theta. That's the force that's pulling the object back toward the equilibrium position. And just to prove that this is linear, I'm going to write down a quick proof of this linear relationship to the displacement from the equilibrium position. I just need to prove to you that this definition also works for pendulums, where there is a linear relationship between the restoring force and the displacement from equilibrium. And there's that relationship, and you can see that it fits y equals mx plus b. One important vocab word for simple harmonic motion will be amplitude. The amplitude of simple harmonic motion is the maximum displacement from the point of equilibrium that the object achieves. This may sound a little simple, but it's actually very precise. So as the spring oscillates back and forth, this green line is showing me the maximum displacement from the equilibrium position. And as it goes in the other direction, it's displaced in that same amount, but again in the opposite direction. So the amplitude is the maximum displacement from the point of equilibrium. So one of these green arrows, one of those lengths, would be the amplitude, because it's the line drawn from the equilibrium point to the far edge. Some students get confused by this and assume that the entire length of the path, the full forward and back motion, is the amplitude, but this is not the amplitude. That's actually twice as large as the amplitude, because the amplitude is only from the equilibrium position to one end, not the entire length. All objects in simple harmonic motion have a period and a frequency. Just as a reminder, period is the amount of time an object takes to complete one full cycle, and it's measured in seconds, whereas the frequency is the amount of repetitions a cycle completes in 1 second, and it's measured in hertz. And hertz, or Hz, really just means events per second. And because of their definition, period is equal to 1 over frequency. So we can calculate the period and frequency of objects in simple harmonic motion. And in simple harmonic motion, the period is specifically the amount of time it takes the oscillation to go to both extremes and then go back to its starting point, not just to one extreme and back. So I'll show you what I mean by that. I'm going to start to time the oscillation of this spring. So this is the starting point of the spring. This is one extreme. It goes back to the starting point, gets to the other extreme of its motion, and then comes back. So that was one full period of motion. And I can see that that took 12 seconds of oscillation. So the period would be 12 seconds. One common mistake is for students to start the object at the starting point, allow it to oscillate to one extreme, and then go back, and stop the time as soon as it gets back to its starting point. But this would not be correct. This says that the period is 6 seconds, which is only half of the full period. So this is what I mean by the amount of time it takes the oscillation to go to both extremes and then back, rather than just to one extreme and then back to its starting point. So the period of this spring would definitely be 12 seconds, not 6 seconds. We use many different types of graphs to show many specific properties of objects in simple harmonic motion at different points along their path. We'll start with the position time graph of an object in simple harmonic motion. So what I'm going to be doing here is measuring the displacement of the spring from its equilibrium position as time passes. So my y-axis shows the vertical height of the spring, and the x-axis shows the amount of time that has passed as the spring's oscillating. And as the spring oscillates, you're going to notice that the graph of its displacement from its starting point over the time that has passed forms a sine wave. There we go. So all graphs of simple harmonic motion will work this way. Pendulums also produce sine wave graphs. And any other object in simple harmonic motion also produces a sine wave or cosine wave graph. We can get some useful properties of the motion from this graph. For example, the height from the center is the amplitude. because that's the total distance from where the center point of the object is, where its equilibrium position is, to one extreme. So that total height of the wave from the center to the top would be the amplitude. Just notice that I'm not measuring from the very highest point on the wave to the very lowest point on the wave. That would not be the amplitude here, just like in the example of amplitude I showed earlier. We can also find the period of the simple harmonic motion graph if time is on the x-axis. The period is going to be one full completion of that sine wave, going all the way up, all the way down, and back to where it started. So again, a common mistake here would be for students to look at the sine wave and say, oh, the period is 6, because that's how long it takes the wave to get back down to its starting position. But the period is 12 seconds, specifically because it has to go up to one extreme, back to the other extreme, and then back to its starting point. That full wave pattern is one period, not just half of the wave pattern. Okay, this is going to be kind of a throwback, but we're going to use the information that the displacement time graph of an object in simple harmonic motion forms a sine wave to find the velocity time and acceleration time graphs of an object in simple harmonic motion. And you'll remember that the slope of a displacement versus time graph is equal to the velocity, and the slope of a velocity time graph is equal to the acceleration. So looking at these slopes, I can see that the slopes of the displacement time graph start positive and go to 0. So that means that the velocity is also going to start positive and go to 0. Next, the slopes become more and more negative, and then become less negative until they hit 0 again. So the same thing will happen to the velocity. It becomes more and more negative, and then less negative until it hits 0 again. Finally, the slopes are getting bigger and bigger and bigger. So that's what the velocity will do until it hits some maximum. So that is what the velocity time graph of an object in simple harmonic motion would look like. So in this particular case, that's actually a cosine wave. We can now translate from a velocity time to an acceleration time graph using the fact that the slope of a velocity graph is equal to the acceleration. So looking at the slopes here, I can see that the slope starts at 0, becomes very negative, goes back to 0, becomes very positive, and hits 0 again. So this is what the acceleration graph will look like. So now we can use these graphs to find more information about objects in simple harmonic motion. One thing I noticed is that the velocity is highest at the equilibrium point and 0 at the extrema. So the equilibrium point is whenever the displacement from the equilibrium point is equal to 0. So there are 3 places on these graphs where the object hits the equilibrium point, here, here, and here. And you can see that when this happens, when the displacement is 0, the velocity is actually at a maximum size. It's either very positive or very negative, but it's never 0. And here at the extrema, where the displacement is at its largest, I can see that the velocity hits 0. So this fits our experience of simple harmonic motion, because when this object is moving in simple harmonic motion, it always moves very fast through the equilibrium position, so that's where Vmax will occur. But then as it gets closer to that maximum or minimum, its velocity goes to 0, and then it goes very fast, and then it hits 0 at the other maximum again. And it keeps oscillating up and down like that. So the fastest velocity always occurs at the equilibrium position, and the velocities of 0 occur at the extrema of the motion. We can also see that the acceleration is highest at the extrema, where the object is not moving, and 0 at the equilibrium point, where the object is moving the fastest. I found that this one is a little more difficult for students to understand, and it's understandably difficult because it's moving very fast through that equilibrium point, but what this is saying is that the acceleration is 0 while the velocity is at its highest value. So whenever the velocity hits a maximum at the equilibrium position, the acceleration actually hits 0. So I'll show you why that is in just a moment. What's extra confusing is at the places where the velocity is 0 are actually the places where the acceleration is the highest. Again, I'll show you why that is in just a moment. So looking at this spring, I know that here the acceleration is 0. And up here, the acceleration is at its max, pulling it back down. And over here at the other extrema, the acceleration is at its max, pushing it back up. So if we think about where the forces are occurring on this object in simple harmonic motion, it makes sense that at the equilibrium position there's no force, so as a result there's no acceleration either. And at the maximum points, the force is going to be at a maximum, pushing the object back toward the center. So that means the acceleration will also be a maximum, pushing the object back toward the center. Another way to understand this is that acceleration being 0 absolutely does not mean that the object is not moving. Acceleration is a change in velocity, so if the acceleration is 0, that just means that the velocity is not changing as it coasts very quickly through the equilibrium position. It's just going through unrestricted, so it just moves at a high constant velocity until it gets to the other side of the equilibrium position and begins to slow down due to the acceleration pointing in the opposite direction. And the point where the velocity is changing the most is where it hits 0, changing from positive to negative. So that's where the acceleration is at a maximum. So that's where the acceleration is at a maximum at the two maximums of the movement, of the displacement. And the acceleration points in the opposite direction of the displacement. So those are all really important central facts to know about simple harmonic motion going forward. Just have a few more basic ideas to cover. First of all, if we made a graph of the force on this object in simple harmonic motion, it would look the same as the acceleration graph, just with an m multiplied by all the values, because force is directly proportional to acceleration. Energy graphs are also interesting and important in simple harmonic motion. Energy is a scalar and cannot be negative. Kinetic energy is proportional to velocity and potential energy is proportional to displacement. So that means that if we were to graph the kinetic energy and potential energy of this spring, that same spring we were graphing before, it would look something like this and like this. So the farther away you are from the equilibrium, the more potential energy you have, and the faster you're moving, the more kinetic energy you have. And these graphs can't go below 0, they can just be either very positive or 0. One interesting pattern here is that because of the conservation of energy, if you add up the kinetic energy and the potential energy together, you'll notice that their total energy always stays the same. If you add the height of the red line and the green line at any point, you'll notice that it always makes the exact height of that purple line, which is just a flat, constant line. The reason why this is happening is because energy cannot be created or destroyed. There's no outside work being done on this object in simple harmonic motion. So that means that all of the energy is staying inside of the system. So whenever it gains kinetic energy, whenever it goes faster, it loses potential energy. It becomes closer to the equilibrium position. For springs, the potential energy we're talking about is elastic potential energy, and for pendulums, the potential energy is gravitational potential energy. So which type of potential energy we use will be different depending on the object, but the kinetic energy is always just kinetic energy. And that's everything that you have to know about basic simple harmonic motion for this course.
This lecture is going to be about phases of a wave. These two waves have the exact same wavelength, period, frequency, amplitude, and velocity, but they still look different from each other. We need one more vocab word to describe the physical difference between two waves. So the reason why we do physics is to describe and understand the world, and if there's a part of the world that we don't have vocabulary for, like the difference between these two waves, we need to invent a new vocabulary term to describe it. Before we talk about this difference, we need to make an observation about the shape of a wave. Any wave graph can be understood as the graph of the vertical height of the radius line of a circle on the y-axis and the angle of the vector on the x-axis. So as this circle goes around, you'll notice that if we track just the vertical height of that radius line as it goes around a circle, that produces a wave. So all waves actually share this property, where they can be understood as the vertical height of that radius line on the y-axis and the degree of the circle on the x-axis. So each of these graphs can show the y-axis height of the radius line for every angle around the circle. So I'm just going to make a graph of the vertical height of the radius line as it goes around the circle, and the x-axis again will have those angles on it in both degrees and radians. What I'm trying to get across here is that certain angles can be associated with certain parts of a wave, and the change in an angle by a certain amount corresponds to the change in a wave by a certain amount. The specific angle that we start from in the circle is kind of arbitrary. We could also make wave graphs that look like this, just starting from different angles around the circle,
and that still produces the same pattern. So the specific angle that a wave is at different points isn't really a constant, but there's something that is constant in the shape of a wave. So the thing that's not arbitrary about the relationship between the angle and the wave is what fraction of the wave a change in angle produces. For example, if we graph the full wave using that circle, no matter which part of the wave we're looking at, a 90-degree or pi over 2 radian change in the circle results in a change of 1/4 of the wave. 180 degrees goes with half the wave. 270 goes with 3/4 of the wave. And 360 goes with the full wave. We can now understand specific fractions of a wave as being equal to specific angles over the full wave. We can use this new way of recording the fraction of a wave to describe how two waves that are otherwise completely alike are at different points in their motion. This is called the phase difference between two waves. This is the difference between which part of the wave's full period or wavelength each wave is on, expressed as the angle difference between the two. Waves at the same point on their wavelength or frequency are said to be in phase. So there's no phase difference between two waves that are perfectly alike. So as an example, I can see that the bottom wave is exactly the same as the top wave. It's just shifted by 1/4 of its length. So that means that the phase difference is going to be 1/4 times 360 degrees, or 2 pi. So the phase difference is equal to 90 degrees or pi over 2. So I would describe the bottom wave as having a phase difference of 90 degrees or pi over 2 from the top wave. Here I can see that the wave is shifted by this much, which is 5/8 of the wave, using that bottom equation for phase difference. 5/8 times 360, or 2 pi, gets me a phase difference of 225 degrees, or 5 pi over 4. This is a displacement time graph, but the exact same rule still works for finding the phase difference. I just need to compare the difference in the waves. And I can see that this is a difference in 7/8 of the wave. So to find the phase difference, I just multiply 7/8 by 360, or 2 pi. And that gets me a phase difference of 315 degrees, or 7 pi over 4. Simple harmonic motion can also be described with phase differences because it can be graphed with the shape of a wave. For example, in this picture, that bottom portion of simple harmonic motion is 3/8 along its full path compared to the original point at that one maximum point of compression. So what's happened here is that that spring that oscillates has been released from rest, moves through the equilibrium position, and continues to move between the equilibrium position and the other maximum. So at that point, it's gone along 3/8 of its full oscillation because it has to come all the way back to that other max for it to be a full oscillation. So because this is 3/8 of its full oscillation, we would say that the phase difference is 3/8 times 360 degrees, which is equal to a 135 degree phase difference, or a 3 pi over 4 phase difference. If it's going backwards, that means that it's already achieved that maximum and is moving back in the opposite direction. So that means that it has now covered 5/8 of its total motion. So the phase difference there would be 225 degrees, or 5 pi over 4. Just one last note, a negative phase difference just means a shift to the left on the graph rather than to the right. So here this graph has been shifted by 1/4 of its period to the left. So that means the fraction of the wave that's been shifted is negative 1/4. So the phase difference is negative 90 degrees, or negative pi over 2. This is the first lecture on waves, and these are the topics we're going to be talking about. This is the definition of a wave. A wave is a disturbance that carries energy through a medium without carrying matter along with it. All waves have common physical properties we can describe and calculate. The particles in the wave exist in simple harmonic motion. So I'm going to play these two animations and have you observe what's happening as the wave moves through the matter. Notice first of all that these two animations show you every particle in the medium that the wave is moving through. So you can see that even though the wave is moving through the medium in either animation that you look at,
The particles themselves are being pushed back and forth by the wave, but they're not really being carried along with it. They're just oscillating back and forth in simple harmonic motion. So this is what I mean when I say that a wave does not carry matter along with it. Any particle that you look at within the matter is moving back and forth, but it's staying within that same region. It's just oscillating back and forth as the wave moves through it. So that part of the definition is really fundamental. To be a true physical wave, it cannot carry that physical matter that it's moving through along with it as it moves. And every single particle inside of that wave exists in simple harmonic motion. It's oscillating back and forth around a point of equilibrium. So we're going to talk about this more as we go through the lecture. There are two wave shapes. We can talk about transverse and longitudinal waves. A transverse wave is a wave that oscillates matter in a perpendicular direction to the wave's motion. And a longitudinal wave is a wave that oscillates matter in a parallel direction to the wave's motion. So I'm going to play these animations and show you what I mean by that. You can see in the transverse wave, the wave is moving from left to right, but if you observe what any one particle in the wave is doing, that one particle is only moving up and down. So the oscillation of the matter is perpendicular to the direction of the wave. The wave is moving from left to right, and the matter is moving up and down. So that's the definition of a transverse wave. That's what makes something a transverse wave. In the longitudinal wave, you can see that the wave is moving from left to right, and the particles in the wave are also oscillating back and forth from right to left to right to left. So they're oscillating in a parallel direction to the direction of the wave. So that's what makes the wave on the right a longitudinal wave. For most tests, you're going to need to be able to list some examples of both types of waves. I'm going to go through some examples of each right now. One example of a transverse wave is a string in a musical instrument. You'll notice that transverse waves are being created when this person plucks the guitar strings. So this occurs with all stringed instruments. Moving a slinky up and down, we can actually use slinkies for both types of waves, but here, this is an example of a transverse wave. Doing the wave at a sports game is also an example of a transverse wave because the wave is moving along the stadium, but the people themselves are moving up and down in a perpendicular direction to the wave's motion. I'm going to add here that electromagnetic waves are also transverse. You don't know what those are yet, so we'll talk about that more later. For now, you'll just have to remember that that's another example of a transverse wave. A common example of a longitudinal wave is sound, because sound is just another example of a wave in matter. Normally we hear it in air particles specifically. You can see in this animation, I'm showing all the individual air particles that are bouncing up and down or left and right as the sound wave moves through them. So you can clearly see the wave radiating outward from the speaker in the center, but if you watch any one particle, you'll see that that one particle is bouncing forward and back and isn't being carried along by the wave. And if you look at the oscillation of any one particle, you'll notice that that oscillation of that particle is parallel to the direction of the wave's motion at that one point. So I've highlighted the particles on the left and right of the speaker, but even if you look in the up or down direction, you'll see that where the wave is moving up, the particles are moving up and down, and where the wave is moving down, the particles are also moving up and down. Slinkies are also useful for creating longitudinal waves because you can push them forward and back like this and create this wave pattern. So this is another example of a longitudinal wave. Another difference to note is the difference between mechanical waves and electromagnetic waves. So a mechanical wave is a wave that requires a medium to move through, some substance to move through. It oscillates matter, and it can be transverse or longitudinal. So just as an example, an ocean wave requires the ocean in order to exist in the first place. If there wasn't water, we wouldn't really be able to describe ocean waves at all. So mechanical waves are any wave like that that needs some medium to move through in order to exist. If there's no medium, the wave itself does not exist. Electromagnetic waves are a special type of wave. It's the only type that moves through empty space. Electromagnetic waves are created as a result of the vibrations between electric fields and magnetic fields. All electromagnetic waves are photons, which are particles of light, and all move at the exact same speed, the speed of light, which we call lowercase c in physics, and that speed is 3.00 times 10 to the 8th meters per second. The only way they're different from each other is in their wavelength and frequency, but their velocity stays the same at that speed of light. So those are some basic definitions of waves that you will need for this unit. This is another video on waves. This is what we're covering here. In this video, we're going to be talking about the specific properties that all waves share, whether they're transverse or longitudinal or mechanical or electromagnetic. So we know that any particle in a wave exists in simple harmonic motion. We can imagine this wave moving through a red string as an example. The blue particle on the string is moved up and down in simple harmonic motion by the wave as the wave moves through it. Like other forms of simple harmonic motion, a wave has an amplitude, period, and frequency. So we're going to start by talking about the amplitude of this wave. So I'm going to start this wave moving and then begin to talk. So you'll remember in simple harmonic motion that the amplitude is the maximum displacement from the center that the object achieves. So you can see that these green lines here each show the amplitude that the particle has achieved from the center point. So just like in simple harmonic motion, where we say that the amplitude is measured from the equilibrium position, the center, to the extreme, we also say that for waves. So this length in particular is the amplitude of this wave. It's the displacement from the center of the wave. Waves can also have a period and frequency. Just a reminder that a period is the amount of time it takes something to complete one complete cycle. So here, if I start this clock and observe how long it takes this particle to complete one full oscillation, I can see that it took 6 seconds. So that means that the period of this wave is 6 seconds. So the period of a wave tells you how long any one particle within a wave takes to complete one full cycle of the wave. And the frequency, as you know, is just 1 over period. So in this case, that would be equal to 0.167 hertz, or 0.167 repetitions per second. So the frequency of the wave just tells you how often the wave repeats in 1 second. This is some arbitrary but important vocabulary. We call the highest point of a wave the crest of a wave, and the lowest point the trough of a wave. So these are crests and troughs of a single wave. All waves also have a wavelength, the length of one complete wave pattern. The variable that we use for wavelength is the Greek letter lambda. It looks kind of like an upside down Y, and the unit is meters or m. So one full repetition of a wave looks like this, like one complete sine wave like this. So the horizontal length of this wave is going to be equal to the wavelength of the wave. That's what we mean when we talk about the wavelength. The wavelength can be measured as the length between two consecutive crests or two consecutive troughs of a wave. So you'll notice that here, by measuring between two consecutive troughs, I can also find the exact wavelength of the wave. That's the same length as what I measured before, and it's the same up here if I measure between two crests of the wave. A common mistake is for students to only identify the length of half the wave as the full wave. They'll see like, oh, this looks like a complete pattern, so this must be the wavelength, but that's actually only half the wavelength. Longitudinal waves have areas of compression and areas of rarefaction. These correspond to the crests and troughs of the wave. The length between 2 points of compression or 2 points of rarefaction is the wavelength. So this is what I mean by compression and rarefaction, where the wave is stretching out the matter versus where it's compressing the matter. So the wavelength is the distance between any two of those points, either two consecutive points of compression or two consecutive points of rarefaction. And that's what you need to know about the basic physical properties of a wave. This is the next video on waves. This is what we're going to cover in this video. I want to start this video by having you observe a pattern that's going to be very important to understanding the rest of this video. I'm going to allow this wave to move for one full period of its motion, and I'm going to observe how much displacement it covers in that one period of time. So one full period will be the amount of time it takes this particle to move all the way up to the top of the wave, and then all the way back down to the very bottom. So let's see how far the wave moves in that one period of time. Okay, this may be kind of intuitive, but in one full period of motion, the wave moved exactly one wavelength of length. And there's no way that couldn't have happened. Like, when you stop and think about it for a little while, a wave has to move exactly one wavelength in one period of time. So this will always be true for any wave that we deal with. Any existent wave at all, in one full period of repetition, a wave moves exactly one wavelength of displacement. So that means that we can come up with a new equation for the velocity of a wave. We know that velocity is displacement over time, and because the displacement the wave covered is its wavelength and the time it took is the period, we can say that the velocity of any wave is its wavelength divided by its period. And because period is equal to 1 over frequency, I can rearrange this equation and say that the velocity of a wave is always exactly equal to its wavelength times its frequency. This is going to be a really important equation for problem solving in this unit. I'm going to give you some more visual intuition about how this equation works. So again, the velocity is the specific amount that this wave will move in 1 second. The wavelength is the length of one complete pattern of a wave. And the frequency is the number of wavelengths that will pass in 1 second, because frequency means repetitions per second. So the number of full repetitions of waves that pass in 1 second is the frequency. So to visualize this, I can see that here I have a wavelength of 3 meters. I'm going to imagine that we have a frequency of 1 hertz, 1 event per second. So this equation is telling me that if I have this wavelength and this frequency, it's going to result in a velocity of 3 meters per second. So let's now use this visual to see if that's... I'm going to have a frequency of 1, so that means that 1 wavelength will pass by in 1 second, and we'll see how much displacement it covered. So 1 wavelength passed by, so I can see that that frequency was 1 hertz, and the wavelength was 3 meters, so that automatically implies that the velocity it was traveling was 3 meters per second. It traveled exactly 3 meters from where it started in that 1 second of travel. We can imagine now that the frequency is 2, that 2 wavelengths will pass by, and each wavelength is 3 meters long, so that means that the velocity is going to be 6 meters per second. And if I allow this to happen, I allow 2 wavelengths to pass in 1 second because that's the frequency. I can see that, yeah, altogether that velocity was 6 meters. It traveled 6 meters in 1 second, so the velocity is 6 meters per second. I can change the wavelength and imagine this is now a wavelength of 1. And if I give that a frequency of 1, so that 1 wavelength passes by in 1 second, I can see that the velocity was 1 meter per second and only traveled 1 meter in that 1 second. Finally, we can imagine a frequency of 4, so 4 of these wavelengths are going to pass in 1 second. And when I do that, I can see that the velocity is again the frequency times the wavelength. So again, that's 4 meters per second here. We can make 2 types of graphs of a wave, a displacement distance graph and a displacement time graph. A displacement distance graph shows the displacement of the material that the wave is moving through for each distance along the material. It's basically a 2D picture of the full wave. So as you can see here, I have a wave with a height from the very top to the bottom of 1.5 meters and a length of 4 meters. So if I were to make a displacement distance graph, the graph on the right would be what it would look like. I have sections of the wave clearly marked off leading up to 4 meters. I can see that the amplitude is going to be 0.75 meters because that's how far the highest point is from the midpoint of the wave, not from the very bottom. So this graph shows you the displacement of the material for any distance along the material that you're looking at. We can use the displacement distance graph to find the amplitude of the wave and the wavelength of the wave. So the amplitude I can see is 0.75, that's how far it is from the 0 point. And I can see that the wavelength is 2 meters because one full repetition of that wave covers 2 meters. So we can use the displacement distance graph to find amplitude and wavelength. We can also make a displacement time graph of the wave. This is a little more complicated. A displacement time graph shows the displacement of one particle in the material that the wave is moving through on the y-axis and the time that has passed on the x-axis. So I'm going to show you an example of making a displacement time graph for this wave. I'm going to only focus on this one point because the displacement time graph only focuses on the displacement of one particle in the material that the wave is moving through. So I'm going to kind of ignore the rest of the wave and just focus on this one particle and what it's doing as the wave moves through it. I've sectioned off 8 seconds on this graph, so I'm going to allow the clock to run for 8 seconds and observe how the particle oscillates as the wave moves through it. And for every moment in time, I'm going to graph the vertical displacement of the particle on the graph. So I'm going to make a red line that shows exactly how high up the particle is for any 1 second of time. So just observe what happens when the wave begins to move through the material. Okay, so that itself produced a wave pattern, but remember, this is not a physical depiction of the full wave. This is a depiction of what one particle in the wave is doing for every moment in time. We can use the displacement time graph to find the period and frequency of the wave as well as the amplitude. So I can see here that the period is 8 seconds. That's the amount of time it took to complete one full wave pattern. So one full wave pattern on the displacement distance graph represents the wavelength, and one full wave pattern on the displacement time graph represents the period of the wave. And because frequency is 1 over period, we can always get the frequency as well. Here the frequency is 0.125 hertz, just 1 over 8 seconds. And obviously the amplitude is still 0.75 meters, that didn't change. We can combine info from both graphs to solve for the velocity of a wave. So because we can use the displacement distance graph to get the wavelength of the wave, and we can use the displacement time graph to get the period of the wave, we can combine these two pieces of information along with the fact that frequency is 1 over period to find the velocity, because to find the velocity, you just need the wavelength and the frequency. So if you have a displacement distance graph and a displacement time graph, you can get the wavelength from the displacement distance graph, the time from the displacement time graph, and put them together to solve for the velocity. So here the velocity would be wavelength times frequency, which is 2 meters times 0.125 hertz, which is equal to 0.25 meters per second. So that is definitely the velocity of the wave, and I can get that from the properties of these two graphs without observing the wave itself. We can also create graphs of motion given the other graph and the velocity. I can imagine here that the velocity of this wave is 0.33 meters per second, and figure out what the displacement time graph would look like. Because if the velocity is 0.33 meters per second, and I can see that the wavelength of the wave is 2 meters from the displacement distance graph, and the amplitude is 0.75 meters, plugging this into my velocity equation and rearranging to get the frequency, gets me a frequency of 0.165 hertz. And the period is 1 over the frequency, and when I divide that out, I get 6 seconds. So that means that this wave has a period of 6 seconds and an amplitude of 0.75 meters. So if I draw that out on my graph, this is what that looks like, an amplitude of 0.75 meters and one complete wave pattern in 6 seconds. So that's what you need to understand to use displacement distance graphs, displacement time graphs, and calculate the velocity of a wave. This video is about electromagnetic waves. The exact physics definition of electromagnetic waves is periodic variations of electric and magnetic field intensity that move through space. The oscillating electric and magnetic fields exist at 90-degree angles to each other and are in phase. EM waves are sometimes called EM radiation. You know these better as waves of light. This is what light fundamentally is. Microwaves, radio waves, infrared waves, gamma rays are all examples of electromagnetic waves. They're all fundamentally the exact same thing. The only difference between a wave of light and a radio wave or a gamma ray is the wavelength and frequency of the wave. You can see I have a picture here of an EM wave with the varying electric field indicated in yellow and the magnetic field in purple. So you can see that they are 90 degrees to each other and they're in phase. So an extreme on the electric field happens at the same time as an extreme on the magnetic field. I actually had a lot of trouble understanding what this diagram meant when I was learning physics, so I'm going to break it down a little bit more before we go on. So first of all, we remember from previous units that larger arrows indicate more field strength. So what's physically happening here is that this is not actually a three-dimensional wave. This is showing the field strength along a one-dimensional path, just a straight line path. So there are certain points along this path where the electric field becomes very large in one direction. That's where it has a very large arrow in one direction. And the magnetic field becomes very large in one direction. And other places where the electric field and magnetic field are equal to 0. So this isn't actually a three-dimensional shape. What this is a representation of the field strength along a one-dimensional line. This is what it looks like when an EM wave moves. I'm going to examine what's happening at that red dot. This is just a random point that I chose along the line to show you the strength of each field at different times as the EM wave moves along that one point. Right here at the beginning, I can see that because there are no arrows, both the electric and magnetic field are 0. The electric field is 0 newtons per coulomb, and the magnetic field is 0 teslas. And as the wave begins to move through the point, suddenly the electric field becomes very large and it's pointing up, and the magnetic field becomes very large and it's pointing out of the screen. As the wave keeps moving, this is another point where the electric and magnetic field are both equal to 0. And as it keeps moving, this is a point where the magnetic field is pointing into the page, the electric field is pointing down, and then another point where the electric and magnetic fields are both 0. And so this is what the wave looks like as it just continuously moves through that point. So again, this is a representation of the field strength of the electric and magnetic field along a one-dimensional line. This isn't like an actual three-dimensional shape that you can reach out and touch. You can see based on the properties of this wave that it's a traveling wave, not a standing wave. Every point experiences the full oscillation of the wave. And the quote-unquote displacement, which in this case means the change in the field strength, is perpendicular to the direction of motion. For both the electric and magnetic field, those oscillations point perpendicularly to the velocity of the wave. So we say that all electromagnetic waves are traveling transverse waves. Electric fields and magnetic fields can both exist in empty space, so kind of like the field of gravity can definitely exist in empty space, electric and magnetic fields can as well. This means that because EM waves are really just changes in the electric and magnetic field, they're the only type of wave that can travel through empty space and do not require a medium to move through. So in comparison, all other waves do require a medium. It wouldn't make any sense for me to say that, oh, I saw a really large ocean wave the other day, and the ocean wasn't even there. Like, you have to have the ocean to have a wave in the ocean. So every other type of wave requires a medium, but EM waves do not. They can just travel through empty space. So this is how the sun's light is able to reach the Earth, even though there's no medium for it to move through. The wavelength of an EM wave is the length between two crests of the electric or magnetic field strength. EM waves can have any wavelength and frequency. And all electromagnetic waves move at the speed of light, which we call lowercase c in physics. You probably recognize that symbol from E = mc squared, where c is the speed of light. And we say they have this speed when traveling in a vacuum through empty space. So the speed of light is 3.00 times 10 to the 8th meters per second. And because the velocity is always c, all EM waves obey c = lambda times frequency. And because c is a constant, if we increase the frequency of an EM wave, the wavelength is definitely going to decrease, and if we increase the wavelength, the frequency is definitely going to decrease. The crest of a wave is where the most energy occurs, and therefore if more crests of the wave impact an object, more energy is delivered to that object. This means that waves with higher frequencies deliver more energy per time than waves with lower frequencies, and waves with smaller wavelengths deliver more energy than waves with larger wavelengths. A way that I visualize this is to imagine that I'm standing in the ocean, and there's a series of waves with a long wavelength coming toward me, and a series of waves with a shorter wavelength coming toward me, and I just imagine which one I would rather be hit by. And it becomes clear that the shorter wavelength waves are carrying more energy per time compared to the longer wavelength waves. So if a wave has a shorter wavelength and a higher frequency, it's carrying more energy per time than a wave with a higher wavelength and a lower frequency. The only physical difference between different types of EM waves is their wavelength and frequency, and as a result, their energy. We can organize the types of wave based on these properties on a chart called the electromagnetic spectrum. So this chart right here shows me the electromagnetic spectrum. You can see the different types of waves are organized by their frequency and their wavelength. And these are the rough boundaries between the waves. There's no exact agreed upon boundary between some of them. You can see that as you go to the right, the waves have a lower frequency and a larger wavelength, and as you go to the left, the types of waves have a higher frequency and a smaller wavelength. So as you go to the right, there's lower energy, and as you go to the left, there's higher energy waves. Optical waves, for example, actually take up a very small sliver of the EM spectrum compared to most other types of waves. I just spaced them out evenly so they're easier to see. We're now going to go through each type of wave and talk about its properties. Radio waves are the longest wavelength, smallest frequency EM wave. We use radio waves for radio and TV signals, and also cell phone signals and Wi-Fi. Going down the spectrum, we come to microwaves. You can see I've listed the range of possible wavelengths and frequencies for a microwave. Examples of microwaves are the waves that exist inside of the machine microwave, and also radar, GPS satellites, and telescopes. Infrared waves can be used for heat sensors. You can see I've given the range of wavelengths and frequencies. A quick English lesson, the prefix infra means below or further on. So infrared means a slightly lower frequency than red, or further on along the spectrum than red. So we're about to come to the optical section. Optical waves are what we can see with our eyes. It's visible light. You can see I've written the range of wavelength and frequencies, and you'll also notice that I've split up the specific colors by the wavelength and frequency. So different colors that we experience are associated with different wavelengths and different frequencies. The capital T in the frequency is short for tera, and the lowercase n in the wavelength is short for nano. So you can see that as you go from red to violet, the energy goes up, the frequency goes up, and the wavelength goes down. Next on the list is UV, or ultraviolet light. We mostly experience these as harmful rays from the sun that we can't actually see. Ultra literally means beyond, so ultraviolet means a slightly higher frequency than violet, or beyond violet. We're now getting into the more dangerous type of wave, like X-rays. An example is X-rays used by doctors. These can also be used to destroy cancer cells, and X-rays are also used in some telescopes. Finally, gamma rays are the highest frequency, lowest wavelength type of EM wave, and therefore they're the most dangerous. They only really come from nuclear reactions and the radiation from radioactive material. Gamma rays have the highest energy of any EM wave and are therefore the most dangerous. So if you've ever heard people talk about radiation specifically, they're usually actually talking about gamma rays radiated off of radioactive material. Electromagnetic waves occur because a changing electric field actually induces a magnetic field, and a changing magnetic field induces an electric field. So because you have a changing electric field, a magnetic field is induced. It's created. And because it's created, it's changed, and so the changing magnetic field also changes the electric field. So that's why these can oscillate on and on forever. When you create a change in an electric or magnetic field, you create a self-sustaining wave that travels away in all directions. And there are two ways to create a change in an electric or a magnetic field. So there are two ways to produce an electromagnetic wave. This question has appeared on the IB test in the past, so it's important to understand these are the two ways that electromagnetic waves can be produced. The first way is to accelerate an electric charge, and the second way is to move an electron from a higher to a lower energy state in an atom. The reason why an accelerated electric charge produces an EM wave is that a moving charge is a current, which we know produces a magnetic field from a previous unit. An accelerating charge, therefore, means a current that is changing its value. Because the current is a measurement of how much charge is moving by per second, so if the charge is moving faster or slower, that changes the current. So that change in the current induces a changing magnetic field, and it also changes the value of the electric field because the particle is moving from one place to another. So because you were able to induce a changing electric field and a changing magnetic field, you create an EM wave. And as the electron in an atom moves from a higher to a lower energy state, it releases its energy that it lost as an electromagnetic wave. What I'm saying right now is obviously a little vague, and there are much better explanations of this process, but this process doesn't really appear much more than this when it's tested on the IB test. So I'm going to leave some links in the description to this video that explain the creation of electromagnetic waves in much more detail. But this is all that you'll need to know about EM waves for this class specifically. This lecture is about standing wave patterns in physics. So far, all of the waves that we've talked about have actually been traveling waves. A traveling wave is a wave where the maxima and minima move continuously through the material they're in. So if you look at any one point in the material of the wave, that one point is going to be oscillated completely by the wave as the wave moves through it. There's no part of the material that doesn't oscillate as the wave moves through it, and the wave moves continuously through the material. The new pattern we're talking about in this video is a standing wave where the maxima and minima stand still in place and do not move. The wave oscillates by flattening out and then achieves the maxima and minima again. So you can see in the animation on the right, that is an example of a standing wave, and you can see how it's different from the traveling wave. Its maxima and minima oscillate up and down, but there are also certain points on the wave that actually do not oscillate at all, they just stay in place. This seems like a pretty subtle difference, but standing waves are really key to understanding a ton of stuff that happens in physics. Standing waves are actually the result of the superposition of two traveling waves with the same wavelength and frequency moving through each other. As their amplitudes add together following the rules of superposition, they produce a single standing wave. Here the blue and red traveling waves are moving through each other and adding to produce the black standing wave oscillating up and down. This pattern is going to be essential to understanding everything else that happens in this series on standing waves. You have to understand that a standing wave is really just the superposition of two traveling waves moving through each other like this. So I would honestly take just another second to observe the pattern that you're seeing here and make sure you understand how that standing wave is forming. It's just the sum of the amplitudes of the two waves moving through each other following the rules of superposition. All standing waves share certain properties. Nodes are point on the standing wave that do not move at all. This is where destructive interference is always occurring between the two traveling waves, making the standing wave. So at every node, that's the exact point where the two waves are canceling each other out to produce a total amplitude of 0. So those nodes do not oscillate at all. The material in the nodes of a standing wave does not oscillate up or down at all. It just stays in place. Antinodes are the points on the wave that move the most, so the places where it reaches its maximum and minimum displacement are the antinodes of the wave. The wavelength and amplitude of a standing wave follow the same pattern as a traveling wave. Sometimes students can get a little confused by the wavelength and assume that the length is just the distance between two nodes, but it's still the length of one complete wave pattern going all the way up and then all the way down and then back to where it started. So that purple line shows the full wavelength of this standing wave. And the amplitude is just from the center point to the maximum point, not from one extreme to the other extreme. So not from the very minimum bottom of the wave to the very top of the wave. The period of a standing wave is the amount of time an antinode takes to go from one extreme to the other and back. The frequency is the number of these repetitions completed every second. This is another really central fact about a standing wave. It has the same wavelength and frequency as the two traveling waves that make it up. So if you observe how many complete traveling waves pass by a certain point in 1 second, that's exactly equal to how many oscillations the standing wave makes in 1 second. So the period and frequency of the two traveling waves are equal to the period and frequency of the standing wave. If I count the total period for the standing wave, the time it takes to oscillate from the top to the bottom and back, I can count 1, 2, 3, 4. So this seems to have a period of about 4 seconds. And if I watch at any one point that the traveling wave is moving through and count 1, 2, 3, 4, that's the time the traveling wave takes to complete one full motion through that point. Because a standing wave has both a wavelength and frequency, we can also talk about it having a velocity in quotes, because the velocity of a wave is equal to wavelength times frequency. And when we talk about the velocity of a standing wave, we really mean the velocity of the traveling waves that make the standing wave up. We can use these interchangeably because the traveling waves have the same wavelength and frequency as the standing wave. So because the standing wave is standing, obviously it's not actually moving at, say, 3 meters per second, but it can still have a velocity, because when we talk about velocity, we can really be referring to the traveling waves that make it up. So as an example problem, we can ask if the period of this standing wave is 4 seconds, what is its velocity? I can see that because this total length is 8 meters, the wavelength is going to be 4 meters because that total length is 2 complete wavelengths. The period is 4 seconds, which means that the frequency, which is always 1 over period, is equal to 0.25 hertz. So the velocity is wavelength times frequency, which is equal to 1 meter per second. So even though the standing wave is not actually moving from left to right, we can still describe it as having a velocity of 1 meter per second because it has a wavelength and a frequency. So that's the intro information that you need to know about standing waves. This video is going to be about the harmonics of standing waves, which are patterns that form at certain frequencies and wavelengths in a material that has a standing wave in it. We're going to start with the harmonics of a material that is fixed at both ends, that can't oscillate on either end. One important note before we start is that the velocity of any wave in a medium is the same as all other waves in the same medium. This is always a little bit surprising to students when they first find it out, but it is true. As an example, all sound waves in 20 degrees Celsius air move at 343 meters per second. All waves in a pond with the same temperature throughout move at the same velocity. So if you have the same medium, the same type of wave will move through it at the same velocity as all other waves in that medium. This is going to be really important for the harmonics of standing waves. This means that for any material, an increase in frequency will cause a decrease in wavelength, a decrease in frequency will cause an increase in wavelength, but neither will change the velocity of the wave. If the wave is in the same material, it will always have the same velocity. So that means that if you change either the frequency or the wavelength, that's going to cause a change in the other rather than a change in the velocity. Let's say that we have a material fixed at both ends so that it can't move. We'll begin to send waves through it to create a standing wave. Because the ends are fixed, they can't move, the only time standing waves will occur is when there are nodes at both ends of the material. Because nodes are places on the standing wave that do not move. So if the endpoints can't move, they have to be nodes for the standing wave to work. So let's observe which standing waves we could make with nodes at both ends of this rope. This is the first example. We can imagine this rope oscillating up and down in this way. So you can see here this pattern has 2 nodes and 1 antinode in the middle. We could also make this pattern. We're allowed to make any pattern that has a node at either end. So this pattern would also work. So this pattern is another possible standing wave in this material. You can see this time there are 3 nodes and 2 antinodes. This is another pattern that would work because, again, we just need to have nodes at either end of the material. And this is another pattern that would work. Each possible standing wave in a material is called a harmonic of that material. For now, I'm going to say that we number the harmonics by their antinodes. It's actually a little bit more complicated than that. I'll explain that later in the video. For example, a harmonic with 3 antinodes is called the third harmonic. We can identify physical patterns in the shapes of the harmonics, so I'm going to take you through each harmonic and observe certain patterns that emerge. We also refer to the first harmonic of a material as the fundamental harmonic or fundamental mode of the material. Just to visualize what's happening at those fixed endpoints in terms of the reflection of waves, as one of the waves moves into that fixed point, we know that it's reflected and inverted by the rule for reflecting waves. And you can see that when that one traveling wave crest moves into the fixed point, it's reflected back, and those total amplitudes always add together to make 0 because they're perfectly balancing each other out. I'm going to observe that one more time. Those two amplitudes always add to 0 at the very end of the material because they're perfectly balancing each other out. So the traveling waves that make up that standing wave are constantly being reflected and inverted at the endpoints. And because they're being reflected and inverted, you can see that their amplitudes are perfectly canceling each other out. So if I were to look at the amplitude of the standing wave there, that's always going to be an amplitude of 0 because the amplitude of the traveling waves are canceling each other out. So that's how our understanding of the reflection of waves helps us understand the behavior of standing waves in different types of material. So for material that's fixed at both ends, the reason why there's a node there is also because the waves are reflecting and inverting. And so at the very end, their amplitudes always add together to make 0. This is a visualization of that same process, just stretched out to a full standing wave. So you can imagine that the blue wave is actually just a reflection of the red wave moving in the material. So when the red wave moves to the left and hits that fixed point at the end of the material, it's reflected and inverted and becomes the blue wave. The blue wave moves back through, is eventually reflected and inverted at the other fixed point, and becomes the red wave again. So this is another reason why fixed endpoints are always nodes on a standing wave in a material. I'm now going to find some patterns in the harmonics of this material. To start with the notation, we can call the wavelength of each harmonic lambda with some number next to it, where n is the number of the harmonic. There's a mathematical relationship between the length of the material, the number of the harmonic, and the wavelength of the standing wave. So let's observe what that is. I'm going to imagine that I have a material of length L. I'm imagining that this is a rope. And I'm going to create that first harmonic shape in it and observe some patterns about the wavelength and frequency of the standing wave in its first harmonic in a material of length L. I can see, first of all, that if I draw out the full wavelength of that wave being created, that full wavelength is actually equal to 2L, 2 times the length of the material that the wave is being created in. So here, in a material that's fixed at both ends, we would say that the wavelength of the first harmonic is equal to 2 times the length of the material. This will always be true. In the second harmonic here, I can see that the wavelength is exactly equal to the length of the material. In the third harmonic, I can see that the wavelength is equal to 2/3 of the full material. And in the fourth harmonic, I can see that the wavelength is equal to 1/2 of the length of the material. I can see there's a pattern emerging where the wavelength of a certain harmonic is equal to 2 over the number of the harmonic times the length of the material. This pattern will always hold for material fixed at both ends. We can use the equation for the wavelength of a harmonic and the fact that the velocity remains the same in the same material to find the frequency of each harmonic. I'm going to use this notation for the frequency of different harmonics. It's just f with a subscript number that's going to be the harmonic number. So for example, the frequency of the third harmonic will be called f3. f1 is the frequency of the first harmonic, and it's also often called the fundamental frequency of the material. So the fundamental frequency of the material can be thought of as the exact frequency that you need to oscillate the material to create a single large first harmonic standing wave in that material. For these problems, I'm assuming that the velocity is remaining constant at v. So we know that for any harmonic number, the velocity is going to remain constant because it's the same velocity in the same material. So for any harmonic, the velocity is going to be equal to that harmonic's wavelength times that harmonic's frequency. If I rearrange this, I get the frequency at any harmonic is equal to v over that wavelength. And because I know the wavelength is equal to 2 over the number of the harmonic times L, I can rearrange the equation in this way. So the frequency at any harmonic is the number of the harmonic times the velocity over 2 times the length of the material. And you'll notice that this is equal to the number of the harmonic times the fundamental frequency, because the fundamental frequency of the first harmonic is where n equals 1, so that's just going to be v over 2L. So the frequency of any harmonic is just going to be equal to that harmonic number times the frequency of the first harmonic. So that means that if the frequency of this first standing wave on top is f1, the second harmonic is going to have twice the frequency of the first. And this is true. You can see that in the animation, the second harmonic is oscillating up and down at twice the frequency of the first. It completes twice as many oscillations in the same time as the first one does. So the third harmonic will have 3 times the frequency of the first, and the fourth harmonic will have 4 times the frequency of the first. Another way that I think about these frequencies, this is just the amount that you have to oscillate the wave to create exactly that pattern in the material. If you and a friend were holding something like a jump rope and sending waves through it, it would be pretty easy to oscillate it up and down slowly to create that first pattern on top, but you would each have to move your hands faster to make the second pattern, and even faster to make the third pattern, and even faster than that to make the fourth pattern. So these frequencies tell you exactly how frequently you should oscillate your hands while you're holding the jump rope to make each pattern emerge. This is an example problem that we can solve using our new understanding of wavelength and frequency in different harmonics. This standing wave in a rope with 2 fixed ends oscillates with a period of 0.167 seconds. What would the period be if the wavelength of the wave were 3 meters? So just picking apart the information, I can see that this is the third harmonic. So the period of the third harmonic is 0.167 seconds. So the frequency is 1 over that, which is equal to 6 hertz. And I know that because this is the third harmonic, that's equal to 3 times the fundamental frequency. So the fundamental frequency of this material must be 2 hertz. That's the frequency required to create the first harmonic in the material. We need to know which harmonic the wave will be in when the wavelength is 3 meters. That's what the question is asking about. So the wavelength of this harmonic is equal to 3 meters, and that's also going to be equal to 2 over the number of the harmonic times the length of the material, which here is 9. So multiplying that out, I find that this wave will have to be in the 6th harmonic for the wavelength to equal 3 meters. So just to clarify that, that means that it's going to look like this with 6 antinodes. And you can see that each full wavelength there, going all the way up and then all the way down and then back to the node, is going to be 3 meters long. I know that the frequency of the 6th harmonic will be 6 times the frequency of the first, which is equal to 12 hertz. So to find the period of this wave, I just take 1 over that frequency and I get 0.083 seconds, and that is the answer that I was looking for. So that will be the period of oscillation if the wavelength were 3 meters instead of what it is right now, which is 6 meters. These next 2 sections will be much shorter. I just need to introduce some slightly different rules when one or both ends of the material is free to oscillate. We'll start with just one end that's free to oscillate. So if one end of a material is not fixed and is free to oscillate, the wave will be reflected back without being inverted. You'll remember that also from the wave reflection lecture. If one end of the material is open to oscillate, reflection still happens, but the wave will not be inverted when it moves backwards. So because the wave is not being inverted, the amplitude of the original wave and the amplitude of the reflected wave are actually going to add together to produce a single larger amplitude. So if you watch this red wave be reflected into the blue wave and observe the amplitudes of both, you'll notice that the 2 amplitudes are adding together. So again, as it's reflected, The amplitude of the red and the amplitude of the blue are pointing in the same direction, so that means that they are going to add together to be a single maximum point, the antinode. And notice that they're not constantly at that highest height. They do eventually both drop down to zero, but the antinodes of a standing wave also drop back down to zero. They just go up again to the top after, so they oscillate like that. So these two amplitudes are adding together. So what I'm trying to get across here is that if you have a material with one open end, that open end will always act as an antinode, and the fixed end will always be a node. You can see here, we can imagine that the red wave and blue waves are reflections of each other. When the red wave hits the left side of the material, it's reflected back as the blue wave, and here the blue wave's amplitude is in the same direction when it's reflected back to the right. And so those two amplitudes add together to produce an antinode. When reflection happens on the fixed point on the right, the blue wave is inverted into the red wave, and so the two cancel out at that one point and form a node. So again, for material fixed at just one end, the open end will always be an antinode, and the fixed end will always be a node. Now that we know that the fixed end must be a node and the oscillating end must be an antinode, let's see if we can find a mathematical relationship between wavelength, frequency, the harmonic number, and the length of the material when we have one oscillating end. Here the harmonic number will go up by 2 as we go to each wave. This is confusing notation. I'll explain why we use it in a moment. So you can see instead of going from the first to the second to the third harmonic, we're just skipping straight from the first to the third, then the fifth, then the seventh, and so on. And we're going to see if we can find a total pattern out of that. Again, I'll explain why in just a minute. So to make a standing wave, I just need to place a node at the fixed point and an antinode at the not fixed point. So the simplest standing wave I could make would look like this. This is the first harmonic of that oscillating string. I cannot make a simpler standing wave that has a node on the left and an antinode on the right. So I can see that the wavelength of this wave is actually four times the original material. What I'm looking at there is only 1/4 of a full wave pattern. So the first harmonic here is going to have a wavelength of 4L rather than what we were looking at when we were dealing with two fixed points. There, the first harmonic only had a wavelength of 2L. So these properties change depending on which ends are fixed. If you have trouble memorizing them, just drawing these pictures that show where the nodes and antinodes have to be can help. The frequency is equal to the velocity of the wave over the wavelength, so that's going to be V over 4L. So the very next harmonic here is called the third harmonic. There's no possible harmonic here between the first and the third. So again, it seems like this should be called the second harmonic, especially because it very clearly only has two antinodes. I'll explain why we call it the third harmonic in just a moment. I can see here that the wavelength is going to be 4/3 times the length of the material. Because if you chop that material into thirds and just added one more third, that would be exactly enough for the wave to complete one full wavelength. That means that the frequency is going to be V over 4/3 L, which is equal to 3V over 4L. And you'll notice that that's equal to 3 times the original fundamental frequency. The very next possible harmonic we call the fifth harmonic. It's going to look like this. These are the patterns that emerge. And finally, this is the seventh harmonic. And these are the patterns that emerge here. So you'll notice that no matter what, all of these are following this pattern here. The wavelength is equal to 4 over the harmonic number times L, and the frequency is equal to N times that first harmonic. So before I had said that the number of the harmonic is the number of antinodes, but that's not actually correct. The more precise definition of the number of the harmonic is the number we need to multiply the fundamental frequency by to get the harmonic pattern. And here, in order to form each new harmonic, we actually have to multiply by the next odd integer, not just the next integer. So we call the harmonics the first and third and fifth harmonic, because those are the numbers that we need to multiply the frequency by to get to them. So there's no second or fourth harmonic because no standing wave forms in this material with one open end when you oscillate the material at a frequency of 2 times the fundamental frequency. These standing waves only occur at every odd integer. The last type of harmonic to talk about is when both ends are free to oscillate. Here, again, we can just observe this standing wave where both ends are free to oscillate. You'll notice that the red and blue waves can each be thought of as reflections of each other. And the reflections where, because the ends are free to oscillate, they go backwards but with the same direction of amplitude. Every time they hit the end of the material, they're reflected back with the same direction of amplitude and in the opposite direction of motion, because both ends are free to oscillate. So you can see that this means that both ends of the material are going to be antinodes. We can now begin to draw the harmonics given the fact that the ends of the rope must be antinodes. This is the first possible harmonic with an antinode at each end. We can't just draw the waves as straight lines going from left to right. It has to follow the general pattern of the wave. So to have two antinodes there, we need one node in the middle. So that's going to be the first harmonic. You'll notice here that the wavelength is 2 times the length of the material, and the frequency is the velocity over 2 times that length. The second harmonic can be drawn like this. These are the properties that emerge. This will be the next possible harmonic, the third harmonic. This is the wavelength and frequency. And this is the fourth harmonic here. And so a standing wave with material not fixed at either end actually forms the same pattern for the wavelength and frequency as the standing wave when the material is fixed at both ends. The wavelength of the nth harmonic will be 2 over n all times L, and the frequency of the nth harmonic will be n times that first frequency. Those are the patterns that emerge in the harmonics of standing waves. This lecture is about when sound occurs as a standing wave. When we graph a standing longitudinal wave, where the nodes and antinodes appear depends on which type of graph we're using. On a displacement graph, the nodes are where the compression and rarefaction occur. This is because those are the places on the standing wave where there's the least displacement. There's no displacement. The particles in those compressions and rarefactions of the standing wave do not move at all. So because those particles aren't moving, on a graph that measures the displacement of the particles on the y-axis, those particles that aren't displaced would be nodes. They just stay at 0 throughout the whole time. And you can see that on that top graph, the displacement graph, the nodes line up with the particles that aren't moving in the animation, which is also where the compressions and rarefactions in the wave occur. On a graph of the pressure of the air, the antinodes are where the compression and rarefaction occur. So even though those particles aren't moving, that's where they feel the most or least air pressure from the other particles. When we're dealing with sound, it's more common to use a displacement versus distance graph than a pressure versus distance graph, so we'll use displacement distance graphs for the remainder of this video. You can see that in the standing waves here, the y-axis of the graph is graphing the displacement of the particles. When the particles move to the left, the displacement becomes negative, and when they move to the right, it becomes positive. And there are certain places where the particles are not being displaced at all. These are the nodes of the graph. So those red lines show you where the particles are not being displaced at all, and the midpoints of those lines are where they're displaced the most. When sound reflects off of a surface to create a standing wave, the particles next to the surface it's reflecting off of do not move in the standing wave. This means that the point at which sound reflects off a surface to create a standing wave will always be a node on a displacement distance graph. So you can see here that the particles on the right side of this animation are being pushed up against a wall that the air is reflecting off of and moving back to the left. So the particles at the very edge of that wall are being compressed and then pushing other particles back, but they themselves are not moving. So because they're not being displaced, they always make a node. So the point at which sound reflects and bounces back on itself will always be the node on a displacement distance graph of the longitudinal wave. So that bottom graph is what the displacement distance graph would look like for this specific standing wave. There's a very popular high school demo of standing waves and sound that involves a tube submerged in water and a tuning fork. We hold a tuning fork over the tube submerged in water and hit the fork so that it makes noise. As we raise the tube out of the water, we notice a pattern. So I'm going to imagine that we hit the tuning fork hold it above the tube, and then observe a pattern in the sound as we lift the tube out of the water slowly. So just sit back and listen to what occurs when we hit the tuning fork and move the tube. This pattern exists because the sound is being reflected off the water, creating a standing wave in the tube. At the point of reflection, the standing wave is a node. As we raise the tube, the point on the wave that the opening is at changes from a node to an antinode and back. Because the frequency of the sound doesn't change, it's the same tuning fork, and because the velocity doesn't change, because it's the same material, air, the wavelength also doesn't change. So the standing wave isn't going to stretch out at all. So instead, as we raise the tube, we raise the opening from being at an antinode to a node to an antinode to a node. Once the sound leaves the opening, it's no longer in a standing wave. It's dissipated in all directions instead of moving up and down the tube. This means that the point on the standing wave that the tube is at determines the energy delivered to the air outside the tube. So let's observe that pattern again, this time where we can see the shape of the standing wave. I'm going to observe this pattern one more time. This time I'm going to pay attention to what the air particles inside the tube are doing, remembering that at an antinode, that's where their displacement is the greatest, and at a node, that's where they're not being displaced at all. They're not oscillating at all. So this is starting off at an antinode. So when there's an antinode, you can see that the air particles are oscillating into and out of the tube, so they must be delivering a lot of sound energy to the air outside of them, because sound energy is just the oscillation of air particles. So any air particles directly outside of that tube are getting hit by the air particles inside of the tube, and then that causes a wave to spread out in all directions. So at the antinode is where they're moving the most, so they're going to deliver the most sound energy to outside. I've now moved the tube up to where it's at node in the air, and here you can see that those top air particles just aren't moving at all. And so because they're not moving, they're not going to oscillate any of the air outside of the tube. So there's no sound energy delivered to outside of the tube. Remember, that standing wave pattern isn't going to continue once the sound exits the tube. And so as a result, the only thing that determines the energy being delivered to the outside air is the energy of those particles on the top of the tube. And you can see that those particles are barely moving. And so they're not really going to deliver any sound energy to outside of the tube. We move it up to another antinode and we can very clearly hear the sound again, because again, this is where the most sound energy is being delivered to outside of the tube. And this is another node of the standing wave, so here there's no sound energy being delivered to outside. So that's why that sound pattern emerges as we raise the tube out of the water. Because we can physically hear where the antinodes occur, we can measure the exact distance between two antinodes. That distance is going to be equal to half the wavelength of the wave. Because the tuning fork usually has the frequency written on it, we can use the wavelength and frequency to find the velocity of the sound in the air. So if I listen for that antinode, and then listen for the next one, and measure the distance between those two antinodes, that length is going to be 1/2 of the full wavelength. As an example problem, we can imagine that this tuning fork is 256 Hertz, and we're holding it above this tube. As we raise the tube, the length between two consecutive points where the sound is loudest is 66 centimeters, and we want to know the frequency of the sound in the air. So the wavelength, 66 centimeters multiplied by 2 and then divided by 100 to convert to meters, is 1.32 meters. The frequency is 256 Hertz. So the velocity of this sound must be 335 meters per second. So that's a very straightforward way of calculating the exact velocity of sound waves in air. Standing waves of sound in a tube behave similarly to transverse standing waves in a string or other material. For example, in most problems, if we have a tube with an open end, that open end is going to be an antinode. The reason why the open end of a tube is an antinode isn't because it physically has to be. We only want the open end to be an antinode if we want the maximum volume from the tube. We usually want the open end to be an antinode to get the most sound out of it. This isn't always the case, but in most problems that we do, we'll assume that the open end of a tube is an antinode, again, not because it physically has to be, but only because we're assuming that the tube has been designed to get the most sound out of that standing wave. Just like the fixed end of a rope, a closed end of a tube is a place where sound is reflected, and that's always going to be a node. That is a physical requirement. That's always going to have to be a node of a displacement graph of the sound standing wave. That's a place where the particles that the sound is moving through are not themselves oscillating. So we can get those same harmonics patterns that we got for the string using these shapes. This is what the first harmonic would look like in each shape. And these are the relationships between the wavelength, the length of the material that the wave is in. In the sound example, that material is a tube, and the frequency of the wave. Just like the string with one open end, if the tube has one open end, we skip straight from the first harmonic to the third harmonic. So these are the general patterns that emerge both for standing waves in strings and for standing waves of sound in tubes. So that's what you need to know about the properties of sound as a standing wave. This lecture is going to be about the idea of universal gravitation, which is the idea that we want to be able to calculate the force of gravity and the acceleration of gravity anywhere in the universe, not just on Earth or on other specific planets. So far in physics, we've been using the equation for the force of gravity on planets. F is equal to mass times the acceleration of gravity. And the acceleration of gravity, g, has always been given. On Earth, it's always 9.8. But we don't know where that came from. And we want to be able to calculate exactly how much gravity any one object is putting on any other object. So we're going to need new equations and new variables to go in those equations to predict that. These are the two equations that we're talking about today, and the variables are all written above my head. So we're going to go through them one at a time. I'm going to start by talking about the equation for the force of gravity between any two objects. The big idea here is that every single object with mass creates a force of gravity on all other objects with mass. And the force always points toward the center of the other object. So I have a cart and a baseball, and if I leave them next to each other, they apply a force of gravity on each other. This is very counterintuitive because we don't ever see the effects of this force of gravity, and the reason why is because the force of gravity that everyday objects put on each other is incredibly small, but it is still present, it's still there. And because of Newton's third law, the force of gravity object 1 creates on object 2 will always be equal in size and opposite in direction to the force of gravity object 2 creates on object 1. So those two things will always be the same, regardless of the size of the individual objects. This can be confusing because a lot of students assume that larger objects create larger forces of gravity on smaller objects. For example, if the moon is putting the same force of gravity on Earth that the Earth is putting on the moon, why is it that the moon orbits the Earth and not the other way around? And the answer is that because the Earth is much larger than the moon, it has a lot more mass, and because of Newton's second law, the object with less mass is more affected by the same force of gravity. So it's not that the moon and the Earth put different forces of gravity on each other, they put the exact same force on each other, as all objects do on each other. The difference is not in the forces, it's in the masses of the objects. The more mass, the less you're affected by the same force. So now I'll give you an example of using the force of gravity equation. It's pretty simple on its own. To calculate the force of gravity, you need the distance between the centers of the objects. Here I'm going to imagine that that's 4 meters, and the masses of the objects. I'm going to imagine that the cart is 10 kilograms and the ball is 0.15. If you need to calculate the force between two objects, you're going to use the force of gravity equation, which is equal to capital G times m over r squared. I have the meaning of each variable listed above my head. You can see that capital G is a constant. We call that the gravitational constant. It's always equal to 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. This is constant everywhere in the universe, no matter which two objects you choose. This large g is always going to come into the force of gravity equation between them. And big M and little m just mean the two masses. It doesn't actually matter which mass goes into which one. It doesn't matter which order you multiply numbers. I'm just going to plug in the larger mass into the larger m, so I have 10 kilograms and 0.15 kilograms.
and the distance between them is 4, which is r, so that's going to be 4 squared in the denominator, which is 16 meters squared. And when I calculate that out, I find that the force of gravity between these two objects is 6.25 times 10 to the negative 12 newtons. So that's 6 trillionths of a newton, which is incredibly small, which is why we don't normally observe that force of gravity. If there were no other forces acting on these objects, if they were just free floating in space, they would, over very long periods of time, start to move closer together because of that very small force of gravity. But here on Earth, where there are a lot of other forces constantly interfering with them, we don't really see that force. It's canceled out by the much bigger forces. And I know that because that force of gravity is the same in both directions, the cart is experiencing the exact same force of attraction that the ball is. Let's do another example for force. This time I'm going to use a more realistic example of a normal experience of gravity, where we can calculate the force that Earth is putting on a person due to gravity and the force that the person is putting back on Earth with gravity using that new equation. And you'll remember that we'd expect this force of gravity on the person, because they're on Earth, to be m times g. That's our normal equation for the force of gravity. I'm going to pretend that here the person is 50 kilograms, so we would expect the force of gravity to be 50 times 9.81, which is equal to 490.5 newtons. So we'll check and see if that new equation works and also gets us that same number. So for the new force of gravity equation, we need the mass of both objects. So Earth is the other object in this situation, creating that force of gravity. And if you look it up, Earth has a mass of 5.972 times 10 to the 24th kilograms. And r, the distance between the two objects, this is actually a common misconception. When students are asked what is the distance between this person and the Earth, they're inclined to say 0 because the person is standing on the Earth. But r here stands for the distance between the centers of the object, so you need to find the distance between the person and the center of the Earth, which is equal to the radius of the Earth. The radius of Earth is 6.371 times 10 to the 6th meters. So watch out for that. If you're calculating the force on something on the Earth, you don't want to say that the distance between that thing and Earth is 0. The distance is going to be between the thing and the center of the Earth. So now I have all the numbers I need. I just start to plug that into the force of gravity equation. And when I plug those in, I get 490.7 newtons. So just a little off. I might have made a rounding error here or there, but it's almost 100% accurate. So I can see that these two force equations both work for the force of gravity of something on Earth. But the special thing about the new equation is that this works for any two objects anywhere in the universe, any distance apart from each other. Another common mistake to watch out for is that problems will often say that an object is a certain height above a planet, and students will often mistake this height for the r in the force equation, but this is incorrect. R means the distance between the centers of both objects. So if you're given this height above the planet that the object is at, r is not equal to that height. The total distance between the two objects' centers is going to equal that height plus the radius of the planet. So the actual r that you'll use in that equation is the height above the planet plus the radius of the planet, because that's the true distance from the object to the center of the planet. So misconceptions don't come up too much in this part of the unit. Honestly, the place where students struggle the most is just actually plugging the math into their calculators correctly. So here, parentheses are going to be your friend. You should use parentheses very carefully in every single problem and use them a lot, because if your calculator misreads anything, that's going to throw off your whole problem. And there are going to be a lot of very big numbers with scientific notation, so as long as you're using those parentheses correctly, you should be good. Please make sure to use those. Another trick to use, if you haven't before, is the double E symbol right here. When you press the EE button by pressing the second function button and then the comma button, your calculator inputs a single capital E. That capital E takes the place of 10 to the power of whatever you put next to it. So if I write 6.67 e to the negative 11th, that's equal to 6.67 times 10 to the power of negative 11. You write the coefficient that you want, e, and then the exponent that you want, and that will be equal to coefficient times 10 raised to the power of that exponent. So that's a way that you can make scientific notation calculations easier on your calculator. Okay, that's it for the force equation. We can move on to the acceleration equation. The acceleration equation tells you the acceleration of gravity that any object will experience at a certain distance from another object. So the acceleration is written as lowercase g, which fits how we've been using lowercase g so far. Lowercase g has been the acceleration of gravity, and here lowercase g is still the acceleration of gravity, just for any point and any object that we choose. And that's going to be equal to the same capital G times the mass creating the acceleration of gravity, not the mass experiencing it. So when we normally use lowercase g in previous units, that acceleration of gravity applied to any object on Earth, regardless of the specific mass of that object. All objects accelerate at the same rate of gravity. So the mass that you're going to put into this equation is always going to be the mass creating that gravity. In this case, it's the Earth, rather than the mass experiencing the gravity. In our case, it was whatever we were dropping at the time. And r, again, is just the distance from the center of mass m to the point where you're measuring the field strengths. So the acceleration of gravity strength is also called the gravitational field strength at that point. That's another name for it. So looking at the picture above my head, you can see that any two objects, regardless of their mass, will experience the same acceleration of gravity the same distance away from the center of the object. This is very commonly used in problems asking you to find the acceleration of objects above the Earth by a certain height. So if you were asked to calculate the acceleration of objects a certain height away from Earth, you would use the mass of the Earth as the thing that's creating the acceleration. And the object's distance from the center is going to be the radius of Earth plus the height above the Earth. So that is what you would put into r. And no matter where you look, as long as you're this far from Earth, all objects placed there will experience the same acceleration of gravity toward the center of the Earth always. So regardless of which object we place there, regardless of its mass, every single object will be accelerated by the same rate toward the Earth. One interesting implication of this is that if we give objects of different mass but at the same distance from the Earth, the same tangential velocity, they'll also have the same centripetal acceleration because they'll have the same acceleration of gravity. They could actually move in circular motion at the same rate around the Earth because they have the same acceleration, same tangential velocity, and same radius. So their mass doesn't determine how fast they go when they are in orbit around the Earth. And this actually holds true if you look at where satellites are around the Earth. As long as satellites are the same height above the Earth, they're going to move at the same rate regardless of their specific masses. So the only thing that determines your orbital velocity around the Earth is actually going to be your distance from the Earth, not your mass. So we can do another test just to make sure that this lowercase g makes sense and try to figure out what would be the acceleration of gravity of a person at the Earth's surface. So we would expect that to be 9.81 meters per second squared. And plugging this into our equation, we know that the mass of the Earth is 5.972 times 10 to the 24th kilograms. The radius is 6.371 times 10 to the 6th meters. Plugging this into our acceleration equation, we get this, which is equal to 9.81 meters per second squared. So this equation explains where we get that value. You'll also notice that if we multiply the acceleration of gravity by mass, we actually get the force of gravity equation, which also fits our expectations because we know from previous units that the force of gravity is equal to mass times the acceleration of gravity. So that is also always going to be true.
This video is about the idea of electric charge. Charge is a property of matter that causes matter to experience the electrostatic force from other charged objects. The more charge the object has, the more force it will experience as a result of another charge. The variable we use for charge is Q, and the unit is C, and it stands for Coulomb, who was a scientist associated with electricity. So charges can be positive or negative. Like charges repel each other and opposite charges attract each other. So you'll remember by Newton's third law, if one charge puts a force on another, the other will put the same force back on that first charge in the opposite direction. So you can see by that picture on the bottom left that opposite charges attract by putting equal and opposite forces on each other, and like charges repel by putting equal and opposite forces on each other. Charge is also conserved. It cannot be created or destroyed, only moved from one object to another. There are only really two types of charged objects in the universe, the proton and the electron. All charge that we experience only exists because of the number of protons and electrons in an object. So there's no other source of charge in the universe. It's just protons and electrons. And protons and electrons have the same magnitude of charge, but opposite sign. So the charge of a proton is 1.602 times 10 to the negative 19th coulombs, and the charge of an electron is the exact same thing, but an electron has a negative charge. So we call this basic number the elementary charge because you can't get any smaller than that. You can't really get a charge that's smaller than that because all charges come from protons and electrons, and there's nothing with a charge smaller than protons and electrons. So all charges really just come in different amounts of the elementary charge. So this means that the charge of an object must be a multiple of the elementary charge. So you can have 1 protons or 2 protons of charge, but you can't have 1.5 protons of charge. That's not possible. So because it comes in these very specific amounts or numbers, we say that charge is quantized, which is a physics way of saying that it comes in specific quantities and it can't take values between those quantities. Charge in an object comes from an imbalance in the number of protons and electrons in the atoms that make the object up. Just looking at this atom, for example, you can see it has 4 protons and 4 electrons. The electrons are in the outer shell. So if I add up the charges here, there are 4 positive elementary charges and 4 negative elementary charges, and so the total charge on this object is 0. If I take away one of the electrons, you can see that it now has a positive charge that's equal to the charge of 1 proton, because the 3 electrons are canceling out the 3 protons, but there's 1 additional proton of charge, so the charge on this atom is now 1.602 times 10 to the negative 19th. And I can keep doing that. I can take away more, and you can see that as I take them away, the charge increases, but it's increasing by the elementary charge. It can't take a value between 2 elementary charges. And so the most positive charge this atom can have is 4 times the elementary charge. I can also add electrons, and then it becomes negative. This leads to a very important observation. Electrons in an atom can move and often leave or join the atom. So they're in the outer shell and they can leave the atom pretty easily and move to other atoms. Protons, in comparison, are stuck in the nucleus. And therefore, when the charge of an object changes, it's almost always because the electrons moved from one place to another, and almost never because the protons moved. So therefore, even when an object becomes positively charged, it is much more likely that this was caused by losing negative charges and not by gaining positive charges. This is going to be a really important concept. Basically, all changes in charge come from the movement of electrons, so even if something becomes positively charged, what that actually means is that it lost negative charge, didn't gain additional positive charges from adding more protons. One last note, you'll have to have a basic understanding of the difference between a conductor and an insulator. A conductor is any material that allows electrons to easily move through it, and an insulator is any material that does not allow electrons to easily move through it. Insulators can still be charged, but the charges stick in place in the insulator and do not move. So common examples of conductors are things like most metals and water, and examples of insulators are things like rubber, air, us, we ourselves are pretty good insulators, wood, things like that, so on and so on. So that's what you need to know about electric charge. This video is about Coulomb's law, which is really just a way of calculating the force between 2 charges. So you can see that Coulomb's law is just a very specific equation that gives the exact force that 2 charges exert on each other. F in the equation stands for the electrostatic force on each object. If F is positive, forces repel, and if F is negative, the forces attract. We'll talk about that more later. K is something called the Coulomb constant. It's just a constant we have to multiply our other numbers by to make sure that we get the right result, and it's equal to 8.99 times 10 to the positive 9 Newton meters squared per Coulomb squared. And again, that's called the Coulomb constant, and its symbol is lowercase k. Q1 and Q2 are just the 2 charges that are putting a force on each other, and the order that you put them in doesn't matter. Either charge can be Q1 or Q2. And R is the straight line distance between the 2 charges. And of course, the force that each charge puts on the other is the same because of Newton's third law. They're the same size and opposite directions. So if you can solve Coulomb's law for one charge, you can solve it for the other charge in the same situation. Coulomb's law is similar to the law of universal gravitation. You'll remember that that's F equals G m1 m2 over r squared. But here there's an important difference where the law of gravitation is always about attractive forces, forces that attract the objects to each other, whereas with Coulomb's law, the forces can also repel. So I've given an explanation in this picture of why a positive force means that the objects are repelling and a negative force means that they're attracting. You can see that because we know that like charges repel and opposite charges attract, if you put 2 positives or 2 negatives into the Q space, you're going to get a positive number, and we know that 2 positives and 2 negatives will both repel. Whereas if you put a positive and a negative into the space for charge, you can see that the result will be negative, because a positive times a negative is a negative, and opposites attract. So that means that if you get a negative force with Coulomb's law, it's going to be an attractive force. The Coulomb is an extremely large unit of charge. We can see using Coulomb's law that if 2 objects charged to 1 Coulomb were placed 1 meter apart, just plugging this in, they would put 8.99 times 10 to the 9th newtons of force on each other. That's 9 billion newtons of force. That's equal to the weight of about 3 Empire State Buildings. So because the Coulomb is so large, most of our measurements will be in microcoulombs. So that's a much more reasonable everyday number. We symbolize a microcoulomb using mu c. Mu is the symbol for micro, and micro means 10 to the power of -6. A common mistake is for students to be given a measurement in microcoulombs and forget to convert it back to regular coulombs before using Coulomb's law. So instead of just saying, like, if you get 50 microcoulombs, you wouldn't just plug 50 into Coulomb's law. You would write it as 50 times 10 to the -6 coulombs. Here's an example. A charge of 3 microcoulombs is brought 2 centimeters from a charge of -4 microcoulombs. What is the force that the charges put on each other? So plugging this in, this is what I know about the charges. And again, I need to convert from microcoulombs to coulombs because that's the unit for the equation. I also need to convert from centimeters to meters because that's the base unit there. So this is the information that I know, and I'm trying to find the force. And when I plug this into Coulomb's law, this is what I get. So I get 270 newtons of force that these two objects put on each other. You can also solve for the net force on multiple charges using Coulomb's law. You basically only have to look at two charges at a time. I'm going to kind of breeze through this and just give you the basic idea of what's going on, and if you want, you can pause and copy down what I'm doing. I'm not expecting you to do all the math in your head here. I'm really just expecting you to see what the process looks like. To find the net force on each charge, I need to start by finding each individual force that the charges are putting on each other. So I'm going to start with these two and just ignore that charge on the top and use Coulomb's law to find the value of the force. And I can see that one of these charges, A, is positive and C is negative. So that means that this is going to be an attractive force. And because of Newton's third law, the force that C puts on A will be equal to the force that A puts on C, just in the opposite direction. And over here, I can see that I've got B and C, and they're going to put an attractive force on each other as well because they're opposite signs. So we'll call that the force from B on C and the force from C on B. Finally, I'm looking at these two, and these are both positive charges, so that means that they're going to put a repulsive force on each other. They're going to push each other away in the opposite direction like this. So I'm going to call that the force from A on B and the force from B on A. So these are all the forces that are present in my problem. So if I can solve for each of these forces individually and then just plug them in and then add the vectors together, I'll be able to figure out what the net force is on each charge. I can see right away there's going to be a problem where I don't know the distance between charge A and charge B, and that's going to be very important for Coulomb's law. But I have a way of finding that because I can see that if I draw that distance between them, it creates a right triangle. So I can use the Pythagorean theorem to find that that distance is 3.6 meters. Next step is to find the angle, because that will tell me the angles of the vectors pointing out of A and B. And I can use some inverse trig to find that angle and see that that angle is 33.7 degrees. And so I know that those two vectors, using some geometry, those two vectors also point at an angle of 33.7 degrees from the horizontal. So these will be the x and y components of those vectors that I can use to add together with the other vectors to find the total net force. And that'll be what those are equal to. So plugging all of these into Coulomb's law, I know that each pair will have the same force going back and forth. So these are going to be the numbers that I get. So starting off on object A, plugging this in, I can see that these are the forces that are acting on it. I'm considering up and right to be positive and down and left to be negative here. And when I plug in the specific forces, this is the total value I get in the x direction and the y direction for the net force on A. So it's pointing 0.81 newtons right and negative 0.46 newtons down. So using the Pythagorean theorem, I can find the hypotenuse, and I can also use inverse trig to find the angle. So there it is. I can do the same process with object B and object C, just plugging in what we know, plugging in the actual values, adding them together. So this is what that total x component and total y component will look like. And now I can find the hypotenuse and angle. And finally, for object C, I can find the net force, plugging it in. These are my values, putting them together, adding the vectors together for the total net force. And there it is. So obviously that was pretty complicated. That was one of the most complicated types of problems we can do in this class, but even that was pretty straightforward. You basically just had to use Coulomb's law on each pair of charges, and then just use some stuff you remember from year one, like geometry and trig and finding the net force and adding vectors together to find the net force on each individual charge. This video will be about electric fields. So let's say that we have a charge of 100 microcoulombs, and we measure out a distance of 5 meters away from that charge, and we place a second charge at that 5 meters. Let's say for now that it's 20 microcoulombs. We can plug this into Coulomb's law and try to figure out the force that that first charge will apply on the second charge. Plugging these numbers in. So this is the equation for the force that that charge will experience. I would just have to convert those microcoulombs into coulombs by multiplying by 10 to the negative sixth. I'm not going to carry out that math. Instead, I want you to observe a pattern. I'm going to imagine now that I replace this 20 microcoulomb charge with a different charge. Just observe how the equation changes. So obviously there's now a 40 microcoulomb charge, so we would just replace one of the charges in the equation with 40 instead of 20, and everything else about the equation stays the same. And if I replace it again, everything else stays the same except for that one charge. And again, everything stays the same except for that one charge. What I'm trying to get at is that if the other parts of the equation stay the same, it seems like there's some property of the equation, those three parts, that are independent of the charge experiencing the force. There's some property of that point in space, just that one point in space, where no matter what charge you put in it, it's going to get multiplied by these numbers specifically. So scientists figured that because that one point in space has this property regardless of which charge is placed next to it, they gave that a special name and called that the electric field. So the electric field, capital E, is equal to the Coulomb constant times the charge that's creating the electric field over the distance from the charge to the point that we're measuring the field strength at squared. So those numbers specifically are the electric field strength. So the electric field is specifically the amount of newtons of force a charge will experience at a given point per coulomb of charge. The field points in the direction that a positive charge would be pushed if placed in the location, and electric field is a vector. The variable is capital E, and the unit is newtons per coulomb. So N times C to the negative 1 means N over C, newtons per coulomb, because it's a measurement of how many newtons of force an object will experience based on how many coulombs of charge that object has. And there are two equations we can use. We'll talk about that more in a second. It can either be equal to K times the charge creating the field over R squared, or it can be equal to the force that a charge experiencing the field is experiencing divided by the charge experiencing the field. Again, we'll talk about that more later. We can imagine that here at this one point, the electric field is 10 newtons per coulomb. And if I plug in a certain charge and I want to know what force that charge will experience, I know that I have 2 coulombs and the field is 10 newtons per coulomb. So if for every coulomb this thing will experience 10 newtons of force, that means that this thing will experience 20 newtons of force from this electric field. We can now imagine that we have a negative 3 coulomb charge, and again the field points in the direction that a positive charge would be pushed by the field. So because we have a negative charge, that would be pushed in the opposite direction as a positive charge, and so it's going to point the other way. The force on this charge is going to point the other way, and because it's negative 3 coulombs, 10 newtons per coulomb times 3 coulombs is equal to 30 newtons, and again, it's going to point in the opposite direction. So this is what the field tells us. It tells us no matter what charge we place inside of that field, the field is going to put this many newtons per coulomb of charge. So we can calculate the electric field pretty easily just by taking our charge, knowing what distance we're measuring from that charge. So here I have positive 50 microcoulombs, and I'm going to measure 10 meters away and see what the field strength is. And already I know that the field is going to be pointing away from the charge because it points in the direction that a positive charge would be pushed. And I know that if I placed a positive charge there, it would be repelled from the other positive charge. So the field will point away. Plugging it into our equation gets me a field strength of 4,495 newtons per coulomb. This is actually a pretty normal field strength just because a coulomb is such a large charge. Once you put in regular sized charges, like in the micro range, it'll go back to being a normal amount of force. Here we can imagine that we have a negative 30 microcoulomb charge, and we're measuring the field strength at 8 meters from the charge. And here, because a positive charge would be attracted to the negative charge, and the field points in the direction that a positive charge would be pushed, the field is going to point toward the negative charge like this. Plugging in my numbers, this is the field strength there. So you can see that I use these numbers in two different ways. The first Q in that first equation is the charge creating the field, and the second Q in the second equation is the charge experiencing the field. That's a really important distinction as we move forward. Some problems will be asking you about a field based on a charge creating it, and another will ask you about the field based on the charge experiencing the field. When you have more than one charge creating an electric field, you can add the vectors together to find the total field. So just imagining that we have a positive and negative charge like this, and we want to know what the field strength is at this blue point. I know that the electric field would point away from the positive charge and toward the negative charge, so there are two different field vectors created by those two different charges. So we would say that the total field at that one point is just the vector sum of those two vectors, like this. So you can use vector math to find the strength, the total strength of a field based on multiple charges. Electric fields are to charge what gravitational fields are to mass. If you multiply the charge by the electric field, you get the electrostatic force, and if you multiply the mass by the gravitational field, you'll get the force of gravity. The electric field shares a lot of other common properties with the gravitational field. I'm going to link to the video we used last year for gravitational fields, just in case you've forgotten about that and want to review. Next thing to know about electric fields are electric field lines, which are lines that show the direction of the field extending out from the charge creating the field. And again, the direction is the direction that a positive charge would be pushed. There are specific rules for drawing field lines that we'll talk about. The lines must begin at a positive charge or infinity and end at a negative charge or infinity. Infinity here just means coming off of the page or going into the page from the outside of the page. The number of lines is proportional to the charge. If you have twice the charge, that charge is going to have twice the number of lines, and no two field lines can cross each other. This sounds complicated, but if I show you a few examples, I think it'll become pretty intuitive. Okay, so following these rules, I'm going to draw some field lines for each of these charges. First of all, I have a positive charge here, positive Q. I don't know exactly what that is. So I'm going to start by choosing how many field lines I want to draw, and I'm going to decide on 4 for now. It's traditional to have at least 8 a lot of the time, but because we're just starting off, I'm just going to draw 4 like this. So these field lines I've tried to make equidistant from each other, like at 90 degrees from each other on each side of that charge, just to make sure that the most area is clear about what the field is doing in that area. So these arrows are not showing the actual field strength, they're just showing the direction of the field at any one point. So basically what these are saying is that if you placed a positive charge anywhere along that line, the positive charge would be pushed along that line in this direction basically forever, which makes sense because that positive charge in the center would be repelling that positive charge away. So if we watch that positive charge move away, we know it's moving away because the other charge, the purple charge, is repelling it. So it follows the field line. The field line shows you how a positive charge would move in that field. So because I just drew those 4 field lines for Q, and I now have a charge of positive 2Q, if I double the charge, I should double the number of field lines that I use. I'm now going to draw 8 field lines coming out of this charge, and it looks like this. And again, this is just showing you for any one point around this dot, these are the directions that a positive charge would be pushed away from that charge. So it's following the rules. They begin at a positive charge and they end at infinity, just going off forever in whatever direction they're going off to. And no two field lines cross. The reason why that rule exists is because if a field line crossed, that would imply that there would be 2 different ways that a positive charge could go from a single point. And that can't really happen. The positive charge is always going to go one very specific way based on the field that's pushing it. Now let's think about what would happen with a negative charge. Well, with a negative charge, the field lines show which direction a positive charge would be pushed. So the positive charge would be pushed toward the negative charge, so the field lines would look something like this. And this follows our rules. Here the lines begin at infinity and end at a negative charge. So those are the only 2 ways that field lines can end. They can't just randomly end in the middle of your paper. They have to go off into infinity or end at a negative charge. There's no other option. And this is because in an actual field, a positive charge wouldn't just stop moving after being pushed around for a while. It would either be attracted to a negative charge or just pushed away forever. And there may be specific points where a positive charge could theoretically be held still by 2 competing charges, but we don't really draw field lines there. I'll show you what that looks like in a little while. So again, this is just because a positive charge would be attracted to the negative charge and follow that path like that. Field lines are often drawn with multiple charges in the same location, so I'm going to show you what that looks like and how to draw those. Here I have a positive charge Q and a negative charge Q, so I'm going to start with the assumption that I'm going to have 8 field lines coming out of the positive Q and 8 field lines going into the negative Q. I have to keep the number of lines equal because the charges are equal to each other. I now have to decide how to connect these field lines, if at all. And basically what I mean by that is I have to determine what types of paths a positive charge would take based on these charges being present. And I can't be 100% certain about this, like there's no way to make these 100% accurately. You kind of have to eyeball it and think about what's going on. Starting with the arrow on the positive Q pointing to the right, I know that if a positive charge were placed there, it would be pushed away from the positive and toward the negative in basically a straight line. There wouldn't be anything to pull it up or down at all. So that's what that field line would look like there. And it obeys the rules. It must begin at a positive charge and end at a negative charge or infinity, which it did. Now, thinking about the two vectors next to that first vector, we can imagine that if a positive charge were placed there, it would arc up, but then back down into the negative charge like that. And the same goes on the other side like this. Like it would probably be pushed away from the positive, but as it moved away from the positive charge, it would feel less force from that, and it would feel more from the negative charge, and so it would begin to be attracted again. For the rest of the field lines, we could assume that they just go off forever like this, because if you put a positive charge far enough away from that negative charge, it might just go on and on forever in that direction. Now let's try the same thing, but this time I've doubled one of the charges. So that means I'm going to need to use twice as many arrows for the left charge as the right charge. So I'm going to choose 8 and 4 like this, and now I need to decide how to connect these. Well, again, a positive charge would probably be just pushed straight in there. And this time, if a positive charge were placed on those other two field lines directly next to that middle field line, the positive charges would feel a lot more force from the positive 2q than the negative q because it has a bigger charge. So they would experience that push away from the 2q for a lot longer than they would feel an attractive force to the negative q. So their path would probably look something like this. And for the rest, we can just imagine that they go off into infinity like that. So that's how I would draw those field lines specifically. Finally, if you have two positive charges like this is going to be a little strange. I'm going to draw the same number of lines for both. I'm going to start by drawing these two lines going towards each other, and this is what they would look like. One reason why they look like this is that electric field lines have to go to infinity and also can't cross each other at any point, so I can't allow these lines to cross each other. Another reason why they look like this is that if a positive charge were placed near one of those positive charges in the middle, it would kind of be repelled from both, so it would be pushed toward the middle, but it would also be repelled up or down, because again, it's being repelled away from both. So if it started just a little bit higher than those two charges, it would just be pushed away into positive infinity. And if it started just a little bit lower, it would be pushed away into like downward infinity, like that. The other lines might look something like this, where it still curves off a little bit because those charges are experiencing the force from the fixed charges. And the others might just look like this, going off into infinity again. So again, these field lines really just represent the direction of a positive charge. They're not perfect. They're not a 100% accurate and precise way of measuring these paths. They're more of a visual approximation. Just make sure that when you're drawing them, you're following those 3 rules. The field strength between two equally and oppositely charged parallel conducting plates is constant at all points between the plates. I could show you the math for that, or you could look it up. I can't really go too deep into that, though, because it's just not really a big focus of the course. You do need to know that the field strength between two parallel conducting plates is the same at every point between the two plates, as long as they're of opposite charge and the same magnitude of charge. But you don't need to know the specific reason why. So if we looked at the electric field strength at any point, it's going to be the same. Like I'm imagining this is 5 newtons per coulomb, so no matter where I look, it's 5 newtons per coulomb. Because a constant electric field applies a constant force on a charge, charges in a constant electric field move in a parabola. So if I were to launch a charged particle into this field, if you think about it, this field is behaving a lot like the field of gravity. It's constant, and on Earth, gravity is a constant 9.8 down, and it's going to apply a constant force, just like gravity does, straight down on this charge. So if this charge is launched into that field, its path is going to follow the shape of a parabola. If you've forgotten why objects with constant forces down move in a parabola, I've also linked the projectile motion video from last year to review. But basically, this is another reason why electric fields are very similar to gravitational fields. And that's what you need to know about how electric fields work. This video is about electron volts and how they compare to joules. An electron volt is a unit of energy, just like a joule. It's usually written as EV, lowercase e and capital V. We use electron volts to measure small amounts of energy. So electron volts and joules measure the same thing, but they measure different quantities of that thing. Specifically, 1 electron volt is the exact amount of energy 1 electron or proton gains when it passes through a region of 1 volt of voltage. So that's the definition of 1 electron volt. That's what electron volts are measuring. So it's literally an electron moving through a volt. And when that happens, you get exactly 1 electron volt of energy in the electron. Because voltage is equal to the change in energy over the charge, I can rearrange this equation to find the change in energy. And I know that the charge of an electron is 1.60 times 10 to the negative 19th coulombs. So because 1 electron volt is the energy that 1 electron gains when it passes through 1 volt, 1 electron volt will be equal to 1.6 times 10 to the negative 19th coulombs multiplied by 1 volt. And because that gets me an answer in joules, This allows me to compare electron volts and joules. So again, they're both units of energy, but 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. So this is how you would go from one to the other. You can use this identity to convert from one back to the other. One way that I remember this is 1 electron volt is literally 1 electron's worth of charge, but as a joule instead of a coulomb, because it's just multiplied by 1 volt to get to a joule. To find the number of electron volts electrons gain, all you have to do is multiply the number of electrons by the number of volts, and that's it. So as an example, if 1 electron passed through a region of 1 volt, it would gain 1 electron volt of energy. If an electron passed through a region of 2 volts, again, you just multiply the number of electrons by the number of volts. So here that's 1 electron times 2 volts. So that's going to result in 2 electron volts of energy being gained by the electron. The reason why that happens is that electron passing through that 2 volt space is equivalent to 1 electron passing through a 1 volt region, just like that first example, and gaining 1 volt, and then passing through another 1 volt region and gaining 1 volt again. So I can see that that would gain 2 volts. Similarly, if I had 2 electrons passing through a 1 volt region, they would also gain 2 electron volts. And the reason why that's the case is that those 2 electrons moving through the 1 volt region are equivalent to 2 individual electrons, each moving through their own 1 volt region. That's kind of literally what's happening there. So I know from my very first example that each individual electron would gain 1 electron volt of energy, so altogether they would gain 2 electron volts. So I can use this to understand the fact that the number of electron volts gained by electrons is equal to the number of electrons multiplied by the voltage. So now I'm ready to do some example problems with what I've learned. Problem 1 says how many joules are in 250 electron volts. So this first one's pretty simple. We just have to convert from electron volts to joules. So I'll use a factor label where I want to get rid of electron volts. So I'll put that in the denominator. I'll put joules in the numerator, and then I'll write numbers next to them to make the numerator and denominator equal to each other. If you're confused about converting units, I've left a video on using this method to convert units in the video description. When I multiply this fraction out, I get 4.0 times 10 to the negative 17th joules, so that's how many joules there are in 250 electron volts. Problem number 2 says how many electron volts are in 2.6 times 10 to the negative 8th joules. So I just take that number, I multiply it by a conversion factor. Here I have joules in the denominator because I'm trying to get rid of joules and replace it with electron volts. And when I do that, this is the answer that I get, 1.63 times 10 to the 11th electron volts. Problem number 3 says 25 electrons pass through 5 volts. How much energy do they gain in electron volts? So the number of electron volts gained is just the number of electrons multiplied by the number of volts. So that's going to be equal to 125 electron volts. Problem number 4 says 30 protons pass through 8 volts. How much energy do they gain in joules? Now, I know that protons have the same magnitude of charge as electrons, so they're also going to gain that same amount of energy. It's just 30 protons, the number of protons times the number of volts. So that's going to be 240 electron volts, but I want that in joules, so I just have to use my method for converting from electron volts to joules. And when I do that, I find 3.84 times 10 to the negative 17th joules is how much energy those protons gained. Problem number 5 says electrons gain 40 electron volts after passing through 8 volts. How many electrons are there? So I know that the number of electron volts is equal to the number of electrons times the voltage. So if I rearrange that equation, I find that the number of electrons, if I divide both sides by voltage, is equal to the number of electron volts over the voltage. So I just plug in my numbers that I'm given, and I find that the number of electrons is 5. Problem number 6 says electrons gain 6.72 times 10 to the negative 18th joules after passing through 7 volts. How many electrons are there? So here I'm going to use the same equation as problem number 5 because I'm trying to find the number of electrons, but I don't have the number of electron volts. I have joules instead, so I'm going to have to convert joules to electron volts. So I'll multiply that by 1 electron volt over 1.6 times 10 to the negative 19th joules. And when I do that, I find that I have 42 electron volts. So I plug in my number, I also plug in the 7 volts to find 6 electrons. So that's what electron volts are. They're just another unit of energy, and that's how you identify their number and use them to solve other problems. This is a quick video on how magnetic fields work. A magnetic field shows the direction that the north pole of a magnet would be pushed by the force of the magnet creating the field. It's a vector. In this class, we only really care about how it affects electric charges specifically. The variable for the magnetic field is capital B, don't ask me why, and the unit is T for Tesla. So I have here the north pole of one magnet and the south pole of another magnet. So if we think about the direction that the north pole of a magnet would be pushed by these two poles, we know that it would be pushed from the north pole to the south pole, like that. So that would be the direction of the magnetic field. Magnetic fields put a magnetic force on moving charges, and moving charges can also create magnetic fields. There are two equations that you'll need to know involving magnetic field. The equation on the left is for a single charged particle moving in a magnetic field, and the equation on the right is for a current carrying wire in a magnetic field. And I find that most of the variables for each of these equations are pretty self-explanatory, except for theta, the angle between the velocity and the magnetic field, or the angle between the wire and the magnetic field. That can be a little confusing, so I'm going to show you what I mean by theta. We can imagine that we have magnetic field lines that look like this. And we can imagine that on the left, I have a charged particle moving in the field, and on the right, I have a current carrying wire in the field. That theta is the angle between the velocity of the particle, or the direction of the current, and the field. And you can see in this instance that both are parallel to the field itself. They're pointing in the same exact direction as the field. So that means that the angle between the velocity and the field and between the current and the field is actually zero. They're parallel to each other, so there's no angle separating them. And if the angle is zero, sine of zero is zero. So that will actually mean that if these things are parallel to the magnetic field, there is zero force coming from the magnetic field on those objects. So this can be a little strange when you first start to work with this, but if you're moving parallel to a magnetic field as a charge, you actually don't experience force. However, if you move in a perpendicular direction to the field like this, you can see that the angle between the velocity and the angle between the current and the field is now 90 degrees. And I know that 90 degrees is where sine is at a maximum of 1. So this actually means that the field is at a maximum if you're moving in a perpendicular direction to the field. So basically, this equation is telling you that it's only the component of the velocity or the current that is perpendicular to the field that creates a force on the object. This is a quick video about 3D vector notation. We're not going to do too much complex math with 3D vectors. You basically just need to know when they appear and how they look and what they symbolize. So far, we've only worked with vectors in 2 dimensions, but we live in a 3-dimensional world. A dimension is an axis of motion that you can move on and that is at a 90-degree angle to other axes. So something that's 1-dimensional has only one axis, like this, whereas something that's 2-dimensional has 2 axes that are at a 90-degree angle to each other, and something that's 3-dimensional has 3 axes that are all at 90-degree angles to each other like this. So again, 1-dimensional, 2-dimensional, 3-dimensional, which is what we're focused on today. So what do I mean by a 3D vector? Well, so far we've dealt with vectors that appear if you were looking at this on your computer screen, like they could point up or down or left or right. A 3D vector would be a vector that could physically point out of your computer like this or point into your computer like that. So how can we symbolize that? How can we use symbols on our 2-dimensional surfaces to symbolize 3-dimensional vectors? To come up with a symbol for 3-dimensional vectors, scientists looked at the vector and thought about where we got this symbol, where the symbol originated. And it probably originated with bows and arrows, like this. And so it's very easy for us to think about what a bow and arrow would look like if it were pointing up or down or left and right on the screen, but it can be a little more difficult to think about what a bow and arrow would look like if it were pointing straight at us or aiming straight away from us. So if the arrow is pointing straight at you, that's equivalent to the vector coming out of the page. Whereas if it's pointing away from you, that means that it's going into the page, like this. So thinking about how you would represent that with a picture, try to think for yourself about what you would draw to show what you would see if an arrow were aiming toward you or perfectly away from you. So scientists decided that the way that we would represent this is if it's pointing perfectly toward you, we'd have a dot that looks kind of like the tip of the arrow. And if it were pointing away from you, we would represent it with an X, because an X kind of looks like the fletching of an arrow pointing away from you, like the tail end of an arrow where the feathers or whatever you're using for stability go. So these are 3-dimensional vectors. They're not too intimidating. If it's a dot, that means it's a vector coming out of your page, and if it's an X, it's a vector going straight into your page. We can't really represent size with these symbols, and we don't even try to do that, especially not in this class. We only really represent sizes of vectors with 2D vectors. So if you see a dot on your screen, that means that it is a vector that is coming out of your screen like this. And if you see an X, that represents a vector going straight into your screen like this. So just as an example, this is what the symbol would look like in a lot of class problems. Here we have a wire, and you can see that to the right of the wire, there are vectors coming out of the screen pointing straight out, and to the left of the wire are vectors pointing straight into the screen, going into the screen like that. So that's 3D vector notation, which you will need a lot in this unit. This is a video about the corner right-hand rule, which is a rule that's used to find the direction of force that a magnetic field is putting on a moving particle or a current carrying wire. So these are the two corner right-hand rules. You can see that if you hold your right hand in exactly this shape, where each finger is perpendicular to the other finger, the thumb, the middle, and the pointer finger are all perpendicular to each other like this. These can accurately give you the relationship in the directions between the velocity of a positive charge, a magnetic field, and a force from the magnetic field on the particle, or the direction of current and the force from the magnetic field on the current carrying wire. So this shape is going to be really important. I'm going to give you an example of using it in just a minute, but while I'm doing that, just make sure that you can make it with your hand, and maybe just look at your partner and see if they can also make the same shape and see if you agree. So just as a quick example of using the corner right-hand rule, we can imagine that we have a magnetic field pointing into the page specifically. These X's mean it's pointing into the page. And we have a positive charge moving this way. If you hold your hand up to the screen and have your pointer finger touch the screen, pointing directly into the screen, and keeping that same shape with your hand, rotate your thumb so that your thumb is pointing in the direction of the velocity of the positive charge, you're going to find that your middle finger is pointing up, like this, like straight up along the screen like that. So because the middle finger shows you the direction of the force, that is the direction of the force on this moving particle from the magnetic field. So that's how you use the corner right-hand rule. I'm going to give you a lot more examples of that in just a moment. Notice that when a charge enters the magnetic field, the field applies a constant force that is always perpendicular to the velocity of the charge. Thinking back to last year, a constant velocity and constant perpendicular force mean the charge will move in circular motion. If you don't remember that, I've left the circular motion video in the description here. This is something that's pretty important that you're going to have to remember. When a moving charge enters a magnetic field, it enters into circular motion because the force kind of follows it along at that 90-degree angle as it begins to turn until it leaves the field. So it will continue to move in circular motion until it leaves the field. The corner right-hand rule can also be used for a current carrying wire. So in this case, this is a wire that's carrying current to the right in a magnetic field that is pointing out of the page. So again, if you aim your thumb to the right and you point your pointer finger out of the page, you'll see that your middle finger is pointing down specifically. So that would be the direction of the force on this current carrying wire. And again, I'm going to do a few examples of using the right-hand rule on a current carrying wire on a piece of paper. Here we're looking at the force that a magnetic field applies on a single moving charge using the right-hand rule. So I'm going to form my hand into that right-hand rule symbol, so all three of my fingers are at 90-degree angles to each other, and just making sure that your pointer finger is pointing out and your middle finger is pointing sideways like this, not the other way around. So starting off here, I remember that my pointer finger points in the direction of the magnetic field. My thumb points in the direction of the velocity of a positive charge. That's going to be important in a little while. And my middle finger points in the direction of the force that's applied on the particle. So looking at this first one, I can see that the velocity is going to the right and the magnetic field is pointing straight down into the page. So I'm going to take my pointer finger and point it straight down into the page and take my thumb and point it to the right. And when I do that, I can see that my middle finger is pointing up specifically, like over this way up on the page. So that must be the direction of the force on that first charge. So the force is always going to be at a 90-degree angle to the velocity in some way or another. Sometimes it will point into or out of the page, but here my middle finger was pointing up, so it's going to point up like that. For the second problem, I'm going to do the same thing, but I remember that my thumb has to point in the direction of the velocity of a positive charge, and this is a negative charge. So we can do two things here. If I use my left hand, the rule will actually work for negative charges, but I find it easier to just say, okay, if the negative charge is going this way, the positive charge would be going in the opposite direction, so I'm just going to take my thumb and point it in the opposite direction of the negative charge. So I take my thumb and I'm going to point it up specifically, and I'm taking my pointer finger and pointing it in the direction of the magnetic field. And when I do that, I can see that my middle finger is pointing straight down into the page. So that must mean that the force from the magnetic field is pointing into the page. So using that vector symbol of an X for a vector going into the page, that is the direction of the force on this particle. For this one down here, you can see it's at an angle, but I can do the same thing. It's a positive charge, so I'll point my thumb in that direction, and I can see here that the magnetic field is coming out of the page. So I'm going to hold my pointer finger up out of the page, and when I do that, I can see that my middle finger is pointing in this direction. So that will be the direction of the force. Finally here, I'm going to use my right hand rule one more time. This is a negative charge, so I'll have to point my thumb down this way, and I can see that the field is pointing in this direction. So I'm going to take my pointer finger, point it in that direction. My thumb is pointing flat down like that, and I can see when I do that, that my middle finger is pointing out of the page. So that means that the force is also going to point out of the page specifically. So that's how you'd find the direction of force for a moving charge in a magnetic field. In this video, I'm going to go over 3 examples of getting other information from the right-hand rule other than just the direction of the force. So for all of these 3 problems, we know the direction of the force, and we're trying to figure out something else using the right-hand rule. In this first problem, we're trying to figure out the direction of the magnetic field. So I'm going to make my right-hand rule again and say that, okay, so I'm trying to figure out the direction of the magnetic field, and I can see that the velocity is pointing this way, and my force is pointing down like this. And I can see that my pointer finger is pointing straight up. So that must mean that the magnetic field is also pointing up. So the answer here is that the magnetic field is coming out of the page. For the second problem, I'm missing the velocity of this negative particle. So again, I'm going to use my right-hand rule and say that the magnetic field is pointing into the page and the force is pointing straight down. And so I would say that, oh, look, my thumb is pointing this way, so that would be the velocity. But my thumb represents the velocity of a positive particle. So if a positive particle would be moving this way, the negative particle would be moving this way. So that would be the velocity for that negative particle. Here I have the field and the velocity and the force, and I'm just missing the sign of the particle, whether it's positive or negative. So I'm going to use my right-hand rule to see which direction I would expect a positive charge to move, and if it doesn't move that way, it's a negative charge. So I'm pointing my pointer finger up, the force is down, and when I do that, I can see that my thumb is pointing in the opposite direction of the velocity. So that means that the positive charge, if this were a positive charge, it would be pointing this way. So because it's pointing in the opposite direction, it must be a negative charge. So that's how you can use the right-hand rule to find other missing information. Okay, let's use the right-hand rule to find the force on each of these current-carrying wires. Starting at the top left, I can see that this current carrying wire is moving current in this direction, and the magnetic field itself, because these are X's, that means the magnetic field is pointing into the page. I'm going to start by forming my hand into that right-hand rule symbol. So I've got my thumb, middle finger, and pointer finger all at a 90-degree angle to each other. Just make sure you're not doing this or anything like that. So you have to make sure it stays in this symbol and that it is your right hand. So I find that it's usually easiest to start by pointing your pointer finger in the direction of the magnetic field, and here the magnetic field is pointing down into the page. So now that I have that, I'm going to keep my pointer finger pointing down, and I'm going to point my thumb in the direction of the current, and the current is going this way. And I can see when I do that, that my middle finger is pointing in this direction. So that must be the direction of force on the wire due to the magnetic field. So that would be the direction of the force in that first instance. We can now look at the top right and see what that looks like, and I can see here that I have a magnetic field pointing to the right this way, and I have this symbol for the current, which means that the current is coming out of the page. A dot or something similar to a dot means that the current is physically coming out of the page. So I'm going to have to use the right-hand rule again, so forming my hand back into that shape. I'm going to point my pointer finger in the direction of the magnetic field, and my thumb is going to point in the direction of the current, which is coming out of the page. And when I do that, I can see that my middle finger is pointing straight up. So that must be the direction of the force here. So because my middle finger was pointing straight up, that would be the direction of the force. Going down here, this one's at an angle, so it's going to be a little weird, but it won't be too bad. So I'm going to say that my pointer finger is pointing in this direction, and my thumb is pointing in this direction like this, because the current is going down like that. So if my pointer finger is pointing like this, and my thumb is pointing down like that, my middle finger is pointing out of the page. So that means that the force on this wire is coming out of the page. It's a dot vector, meaning it's coming out, rather than an X vector, meaning that it's going in. Finally, we have a current going into the page and a magnetic field pointing straight up. So magnetic field with my pointer finger, thumb
pointing straight into the page like that, and I can see that my middle finger is pointing to the right, so that would be the direction of the force on that current carrying wire. This video is about the curl right-hand rule, and we use the curl right-hand rule when a moving current induces a magnetic field. We use the curl right-hand rule because an electric current moving in a wire actually induces a magnetic field. And to find the field's direction, we use this curl rule. So you can see that when the current induces a magnetic field, the magnetic field exists in a circle around that current. So to find the direction of that circular magnetic field, if we hold up our right hand in that symbol and say that the thumb points in the direction of the current, then the magnetic field is going to curl around in the direction that our hand is curling, like that. The curl right-hand rule also works in reverse. If we have a current moving in a circle, it induces a magnetic field coming out of the center of the circle that follows the direction of our thumb, like this. And both right-hand rules can also be flipped in terms of which event is causing which. Current induces a magnetic field, and a magnetic field also induces a current. This is actually how most of our electricity is generated. So I'm now going to transition to a separate video where I'm solving some examples of using this rule on a piece of paper. Okay, in this video we're going to use the curl right-hand rule to find the induced magnetic field from an electric current. So I'm going to have my right hand in the shape of that curl symbol, and we're going to see what we can do. So starting up here, I can see that I have a current going straight up. So that means that I'm going to place my thumb pointing up and see how my hand curls around either side of the page. So I can see right away that on the right hand side, like on this side of the current, my curl is going into the page. And when I hold my thumb up here, the curl is coming out of the page like this. So that means that for the induced magnetic field here, on the right-hand side, it's going into the page. And on the left-hand side, it's coming out of the page. What's actually happening here is that this is forming a kind of circular magnetic field where it's coming out like this, going back in like that, circling around, coming back like this, but we can't really represent that accurately on a 2D surface, so we just record where it's coming out and where it's going in. So that's what that would look like. For the second problem, I can see that the current is coming straight out of the page, so if I hold my thumb coming straight out, I can see that my fingers are aiming in a counterclockwise direction. And if I just follow that along, it's always going to be counterclockwise. So that means that the induced magnetic field is going to be going this way in a counterclockwise direction. For this one down here, I can figure out what's going on inside the field and outside of the field, and this time I'm going to flip the rule and say that I'm going to use the rule where my curl represents the current and my thumb represents the magnetic field that's induced by that current. So if I follow my fingers along this way, I can see that inside of the circle specifically, like inside of this circle, my thumb is always pointing up. So that means that inside of the circle, the field is pointing up out of the page. And if I follow the curl rule like this around this way, and I'm just following my thumb around in a circle, I can see that outside of the circle, my fingers are always pointing into the page. So that means that outside of the circle, the induced magnetic field is going to be pointing into the page specifically. Finally, this one's a little weird. You can see that the current is going up around this coil and going sideways this way as it winds around. So if I curl my hand like this, because I can see it starts off, it seems closer to me and then farther away, closer and then farther away. So it's going to curl like this. So I can see that the magnetic field induced inside of that coil is going to point in this direction. So that's how you would find the induced magnetic field direction from the direction of the current that's inducing it. This is a quick video on combining the right-hand rules. This is a pretty simple concept. I'm going to show you what I mean. Let's say that you have a fixed wire, that means it can't move, and it's carrying a current pointing straight down like this.
Using the curl right-hand rule, I can see that on the left of the wire, the magnetic field is going to be going into the page, while on the right of the wire, the magnetic field is coming out of the page like this. Now let's imagine that I take a second wire, and this time this wire is movable. So this wire can be moved back and forth like this. And I'm going to imagine that the current is also pointing straight down. So you'll notice that because of the magnetic field created by that first wire, that second wire is now in a situation where it's a current-carrying wire in a perpendicular magnetic field. So if I use the corner right-hand rule on that wire, I find that there's a force pulling that other wire toward the fixed wire. And it's being created by the magnetic field that that first wire is creating. So if you have two wires with strong currents that are both pointing in the same direction, they will actually attract each other. And you can see that if we flipped the direction of the current using the right-hand rule, the force will now point in the opposite direction and the wires will be repelled from each other. So this is a pretty simple concept. It's basically just saying, okay, there's a magnetic field created by this first wire. I know how to find that direction using the curl right-hand rule. A second wire experiences that magnetic field, and I know how it will respond using the corner right-hand rule. So that's what I mean by combining two right-hand rules together to predict motion.
This is a quick review of atomic notation and other basic facts about atoms before we move into nuclear power. To start off, atoms are made of just three particles, the proton, neutron, and electron, and protons and neutrons both exist within the nucleus or center of the atom, while electrons orbit outside of it. Both protons and neutrons are referred to as nucleons because they both exist in the nucleus. A nucleon just means a particle that exists in the nucleus of an atom. We use this specific notation in physics and chemistry to describe atoms, where we use a large letter from the periodic table to say which element the atom is. So this is an example of a carbon atom because it's capital C. And then on the top left, next to the letter, we write the number of nucleons, the protons plus neutrons, the atom has. This is also called the atomic mass because most of the mass exists in the nucleus. So if we can know the number of nucleons the atom has, we have a rough idea of the mass of the atom. On the bottom left, you can see we write the number of protons that the atom has, and this determines which element the atom is. So carbon atoms, as an example, can have different numbers of nucleons. They can have 12 or 13 or 14 nucleons, but they can't have a different number of protons. They always have to have 6, and if you have more than 6 protons, you have a different element. It's no longer carbon. So this notation specifically means that there are 6 protons. So if I were to draw a rough sketch of what the nucleus of this atom looks like, I would include 6 protons, these red dots here. And because it has 12 nucleons altogether, and it has 6 protons, and the total number of nucleons is the protons plus the neutrons, that must mean that it has 6 neutrons to give it 12 nucleons altogether. So even though the number of neutrons isn't stated with this notation, you can still find it using the numbers given to you. Like if you know that there are 6 protons and 12 nucleons, there must be 6 neutrons. Because the number of protons determines which element the atom is, changing the number of neutrons does not change the atom's element. However, atoms with different numbers of neutrons behave differently. They're more or less radioactive. So we need a name for atoms of the same element, but different numbers of neutrons, and we call these isotopes of the element. The isotope name is always written as the element and then the number of nucleons. To use this in a sentence, carbon-12 is an isotope of carbon, and carbon-14 is a more radioactive isotope of carbon. So changing the number of nucleons makes the element more or less radioactive. So I've drawn 3 examples of carbon here, carbon-12, carbon-13, and carbon-14, and below them I've drawn what their nuclei look like, what each nucleus looks like. And you can see that each nucleus has the same number of protons, because if it doesn't have the same number of protons, it isn't carbon anymore, but it has different numbers of neutrons because these are different isotopes, so it has to have different numbers of nucleons altogether. This picture is meant to show you that if you add neutrons, that changes the number of nucleons without changing the element, but if you add protons, that changes the element itself. So here you can see that we're going from carbon to nitrogen to oxygen as we go from 6 protons to 7 protons to 8 protons. And I'm keeping the nucleons the same in that lower picture. That actually would mean that I'm subtracting 1 neutron for every proton that I add to keep it at 14. I'm just keeping the number of nucleons the same here, ultimately just to show you that keeping the nucleons the same does not keep the element the same, because if you change the protons, you change the element. Often, information about atoms is just given using their isotope name or number of nucleons. In this unit, as an example, we're going to use uranium-235 and uranium-238 quite a bit. When this happens, you will need to look up how many protons the atom has. You can do that using the periodic table, and that can also tell you how many neutrons the atom has, because the number of nucleons minus the number of protons will equal the number of neutrons.
So as an example, we can ask how many neutrons does uranium-238 have? So I know that uranium is capital U as a symbol, so I would write it like this, a uranium atom U with 238 nucleons, so that goes in the top left. Looking at the periodic table, I can see that uranium is down here, and this table is telling me that it has 92 protons. That's what the top left number means. So I can write 92 down here, and I can use this to figure out how many neutrons uranium has. So the number of neutrons is just going to be the number of nucleons minus protons, so that's equal to 146. So there are 146 neutrons in this uranium atom. Sometimes subatomic particles are emitted from chemical reactions. This happens quite a bit in the nuclear energy plants specifically. And when this happens, we will also need to record neutrons and protons that are emitted from the reaction. So a neutron is just recorded as a lowercase n. You'll notice that subatomic particles are recorded as lowercase, whereas elements or atoms are recorded with capital letters to start off. Subatomic particles are just written lowercase. So the symbol for a neutron is n, and it has one nucleon because it is just that one nucleon, the neutron, and it doesn't have any protons. So a neutron can be written as lowercase n with 1 on the top and 0 on the bottom, and a proton can be written as the same way, but because it is also one nucleon, it has one nucleon, it is itself a proton, so it also has one proton. Those two things are the same, and here we would also say that it has a net positive charge of 1. This one thing isn't going to be too important for this unit, it'll just be important to know for a few context clues. We can use this notation to write chemical equations that show which chemicals exist before and after a chemical reaction. In a chemical equation, the total protons and neutrons before equal the total protons and neutrons after. So as an example, I can add up the total protons before the reaction here, and I can calculate how many neutrons there are using nucleons minus protons for each one. And here I can add up the total protons before and the total neutrons before, and I can see that the total number of nucleons remain the same. In this case, this involves a single neutron bombarding a uranium atom and splitting it up into these other atoms here and 3 additional neutrons. So you'll have to have a basic understanding of what this means, but you won't have to do complex chemical equations in this unit. You are going to have a basic understanding, though, of what's physically happening in this equation. So this just means that one uranium atom is interacting, in this case being bombarded with one neutron, and that neutron is splitting it into these other chemicals with smaller nuclei plus 3 additional neutrons. And you can see that this works because before and after the total number of protons and neutrons are the same. What will be extremely important for this unit, maybe the most important thing in this review lecture, is calculating the mass of a specific amount of atoms. One thing you'll have to know is the definition of 1 mole of a substance. This is equal to the exact amount of a substance equal to the atomic mass times 1 gram. I'll do an example of that in a moment, but this is Avogadro's number. The amount of atoms in 1 mole is equal to Avogadro's number, which is 6.02 times 10 to the 23rd. This is the number of atoms that exist by definition in 1 mole of a substance. As an example, you have 27 grams of carbon-12. How many atoms are inside? So to figure this out, we can take 27 grams and begin to convert it. So I'm going to multiply 27 grams by a fraction, a conversion factor, with grams in the bottom because I want to get rid of those, and I want to convert to moles, because usually the way that we convert from mass to atoms is to use moles as a middle point. I can see that 1 mole of a substance is equal to the exact amount of a substance that's equal to the atomic mass times 1 gram. So if I take the atomic mass of carbon-12 and multiply it by 1 gram, that's how many grams of mass there are in 1 mole of carbon-12. So in 1 mole of carbon-12, because this is carbon-12 specifically, the atomic mass is 12. The atomic mass is just the number of nucleons. So the atomic mass times 1 gram is just 12 grams. So having an atomic mass of 12 means that for every 1 mole of your substance, there are 12 grams of that substance. Multiplying it by another conversion factor, here I want to get rid of moles and change it into atoms. And I know that for every 1 mole of a substance, there is Avogadro's number of atoms. So I'm going to plug that in, 6.02 times 10 to the 23. And I cancel out grams, I cancel out moles. And multiplying this out gets me 1.35 times 10 to the 24th atoms. So that's how many carbon-12 atoms weigh exactly 27 grams. In example number 2, we have 100,000 atoms of uranium-235, and we want to know the mass of the uranium. We're going to start with the number of atoms and convert them into grams. Multiplying by a conversion factor, I want to get rid of atoms, and the mole is always the bridge between atoms and grams, so I'm going to put moles in the numerator. And for every 1 mole, I know that there's an Avogadro's number of atoms, so that's what's going into my conversion factor to make those two things equal. And now that I've gone from atoms to moles, I need to go from moles to mass. So I need to cancel out moles, so that's going in my denominator. And in my numerator, I need to know how much mass of uranium-235 goes into 1 mole of uranium-235. And I remember that a mole is exactly equal to the atomic mass times 1 gram of mass. And here, the atomic mass of uranium-235 is 235. That's what it means. There are 235 nucleons in uranium-235. So multiplying 235 times 1 gram gets me 235 grams per 1 mole. Multiplying all of these things out gets me a final answer of 3.9 times 10 to the negative 17th grams, which is very small. But that's exactly how much mass exists in 100,000 atoms of uranium-235. And that's what you need to know about atomic notation. This lecture introduces the idea of photons and using the Planck constant to find a photon's energy. A photon is a particle. Specifically, it's a particle of light. All light is made of photons. All photons move at the speed of light, which is 3 times 10 to the 8th meters per second. We use the symbol lowercase c to stand in for that constant. Photons are both waves and particles. There's no clear way to visualize this at all. We cannot really represent what a photon really looks like, quote unquote, using pictures, because there's not really a way that photons actually appear. So even though we can't visualize them, I'm going to be using this symbol to represent photons in the lectures going forward. It's not at all what photons actually look like, just a useful visual for a particle and a wave. Obviously, it's very strange that photons are both particles and waves. There are complicated reasons for why they behave like both. I'll go into that a little bit in future lectures, but I've also left some additional lectures in the description of this video explaining it more. So again, that symbol is not at all what photons actually look like. It's just a way to symbolize the wavelength and the particle at the same time. Photons are specifically electromagnetic waves, which is a topic that we've already covered in the course. So if you're watching this and you haven't watched the electromagnetic waves lecture yet, I would encourage you to do that just to have a complete understanding of what kind of thing photons fundamentally are. So that lecture goes into a lot more detail about how electromagnetic waves work and their properties. So this lecture is assuming that you've already seen that video, or at least know the basics of what an electromagnetic wave is. Photons carry energy. We call the energy of light luminous energy. The amount of energy a photon carries is based on its wavelength. Photons with smaller wavelengths and larger frequencies carry more energy. So students sometimes forget whether it's a larger wavelength or a smaller wavelength that carries more energy. And I use this in the EM wave video as well, but I'm going to use this analogy again. I'm going to imagine that I'm standing in the ocean, and I try to think about if the amplitude of the waves are equal, would I rather be hit by a wave with a long wavelength and small frequency, or a short wavelength and a high frequency? And if I think about which one I would rather be hit by, it becomes pretty clear that the wave with the smaller wavelength is going to be much more painful to experience because it's going to be delivering a lot more energy in the same amount of time. So if the wavelength of the wave in water is shorter, it's going to be delivering more energy. And so in the same way, photons with smaller wavelengths and higher frequencies deliver more energy than longer wavelength photons. To understand exactly how much energy a photon carries, we use a physical constant which relates a single photon's frequency in hertz to its energy in joules, the Planck constant. We symbolize the Planck constant with lowercase h. So this is the exact value of the Planck constant. 6.63 times 10 to the negative 34th joule seconds. So what this number is telling me is this is the exact amount of energy in a photon per hertz of frequency. So if a photon's frequency is 1 hertz, that means that the amount of energy it contains is exactly 6.63 times 10 to the negative 34th joules. And if a photon has a frequency of 2 hertz, its energy is 2 times the Planck constant, and if it's 5 hertz, it's 5 times the Planck constant. So the Planck constant is the energy per frequency of the electron. And so an equation for the Planck constant is the energy a photon contains over the frequency of the photon. As a quick explanation of the unit, you'll notice that the unit is joule seconds. I can see that the unit of energy over frequency would be joules per hertz, because hertz is the unit of frequency. If I rearrange that, I get joules times 1 over hertz. And I know that hertz is equal to 1 over seconds, so if I rearrange that to solve for 1 over hertz, I can see that seconds on its own is equal to 1 over hertz. So that means that the unit of energy over frequency is equal to a joule second, joules multiplied by seconds like that. So that's why the Planck constant has the unit that it does. I can prove a few more equations by combining this identity with a few others. First of all, if I rearrange this equation for the Planck constant, I can see that energy is equal to the Planck constant times the frequency. So that's going to be one equation that we use a lot. I can also rewrite this in terms of the wavelength of the wave, because I know that the velocity of a wave is the wavelength times the frequency. Rearranging for frequency gets me velocity over wavelength. And because we're dealing with light, the velocity is going to be a constant c.
So I can replace v with c in this equation. So the frequency of a photon is equal to c, the speed of light, over the photon's wavelength. And I know that c is equal to 3 times 10 to the 8th meters per second. So I can replace f in my equation with c over lambda. And when I do that, this is what I get. And if I rearrange this to find the wavelength, I get this equation here by multiplying both sides by lambda and dividing both sides by e. So these two facts here are constants that you're given on every test. You would never have to memorize the Planck constant or the speed of light. Those are given in your data booklet. And these two equations are also given in your data booklet. So the equation on the top tells you how to find the energy of a photon if you have its frequency, and the equation on the bottom tells you how to find the wavelength of a photon if you have its energy, because you always know the speed of light and the Planck constant. So you would just need to worry about the energy to find its wavelength. So we now have a way of connecting the frequency, the wavelength, and the energy of any photon that we're dealing with. So I'm going to keep these equations up here and do a few examples with them in just a moment. Before we go into that, I just need to note, when we're dealing with photons, energy is often reported in electron volts, or EV. To convert from electron volts to joules, remember that 1 electron volt is equal to the charge of 1 electron multiplied by 1 volt. So multiplying that out, I find that 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. If you've forgotten how electron volts work, I've left a link to my lecture on electron volts in the video description. There will also be times when you need to identify what type of EM wave a photon is based on its energy. To do this, you would solve for its frequency or wavelength and use that to identify where the photon is on the EM spectrum. So again, I talk about this spectrum a lot more in my electromagnetic waves lecture, which I've linked in the description. Okay, let's do some examples with these new equations. What is the wavelength of a photon, which has an energy of 38 electron volts? So we're trying to find the wavelength. We know the Planck constant, that's always given, and we also know the speed of light. And we also have the energy as 38 electron volts. Because the Planck constant works with joules and not electron volts, I'll have to convert to joules before solving the problem. So I'll use the factor label method for that, where I know that for every 1 electron volt, there is 1.6 times 10 to the negative 19th joules. So multiplying that out gets me an energy of 6.08 times 10 to the negative 18th joules. So I now have enough information to solve the problem because looking at my equation, I only have one missing variable, and if I only have one missing variable, I can plug in my numbers. So when I plug in my numbers here, I find that the wavelength is equal to 3.27 times 10 to the negative 8th meters. So that's kind of cool. If you know exactly how much energy a single photon contains, you also automatically know the exact wavelength of the photon. Example 2 says, what is the frequency of a photon with an energy of 112 electron volts? So now we're looking for the frequency. As usual, we're given the Planck constant, and we know the energy is 112 electron volts. Converting that to joules gets me 1.79 times 10 to the negative 17th joules. So the energy is the Planck constant times the frequency. Isolating the frequency there gets me the energy over the Planck constant, so I plug that in. And you'll notice the units also work here, where my final unit will be 1/seconds because the joules cancel out, and that's equal to hertz. So the frequency of this photon is equal to 2.70 times 10 to the 16th hertz. So again, if you're given the energy, you can always automatically calculate the frequency of the photon. Example number 3 says, what is the energy in electron volts of a photon with a wavelength of 6.5 times 10 to the negative 7th meters? So now we're looking for the energy, and we know the Planck constant, and we know the wavelength, and we'll also need the speed of light here because that's going to show up in the equation. So I'll plug this in and start by isolating energy in the equation. When I do that, this is the equation that I get for energy. And then I plug in my numbers, and I get an answer of 3.06 times 10 to the negative 19th joules. But I want that answer in electron volts, not joules, because that's what the problem is asking for. So to convert from joules to electron volts, I use the factor label method. And I find that this is equal to 1.91 electron volts. So that's exactly how much energy a photon would have if it had that exact wavelength. Finally, example number 4 says, what is the energy in joules of a photon with a frequency of 2 times 10 to the 6th hertz? So I'm looking for the energy, I have the Planck constant, and I have the frequency. So this is a pretty simple equation. I just plug it into E equals Planck constant times frequency. And when I do that, I find a final answer of 1.33 times 10 to the negative 27 joules. So that's everything that you need to know about the connection between the frequency, wavelength, and energy that photons contain. This lecture is going to be about electron energy levels and photons.
Before we talk about electron energy levels, it's going to be really important to understand what negative energy means. We've experienced objects that have positive energy. For example, this 5 kilogram bowling ball would have some positive gravitational potential energy, and we know this because it's above some height that we're considering to be a 0 point of height. That position on the ground is where we're saying the bowling ball has a height of 0. So we can imagine that the bowling ball is, say, 8 meters above that 0 position, and we can use the gravitational potential energy equation to find that the total gravitational potential energy there is 392 joules. The important idea here is that that positive energy is defined compared to some 0 point where the ball has 0 height and so 0 energy. So if we were to just drop this ball on the ground, at that exact point it would have 0 potential energy because the height in the equation is 0, and so the whole thing is just 0. So we can understand positive energy and we can understand 0 energy. I want you to imagine now that we dug a hole in the ground and allowed a bowling ball to fall into it. And we can say that this hole is 4 meters deep in the ground. So it would be meaningful to say that this height is negative 4 meters. It's 4 meters below the place that we've defined to be 0 height. And if we plug a negative height into our energy equation, I can see that I get a negative energy as a result. This is negative 196 joules. Does it mean anything that that energy is negative? Does that tell us anything meaningful about the object? I'm going to say here that negative energy does mean something, and it means something unique from positive energy. Because if this ball has negative 196 joules of gravitational potential energy, I can see that if I add 196 joules to this ball, what that means is that the ball is going to be raised to the point where it has 0 potential energy. So negative energy can tell us exactly how much energy needs to be added to get an object back to the normal 0 energy state. You can think about it as being the amount of energy needed to get an object out of a rut or out of a hole and back to the 0 energy state where it has no potential energy at all. So that negative 196 joules communicates that you need exactly 196 joules just to get this object back up to the 0 energy state where nothing's affecting it. I'm going to draw a comparison now between electrons that are just floating in free space unattached to an atom and a bowling ball just sitting on the ground at a height of 0. Here, because the electron isn't attached to an atom, we would say that the electron is just moving freely in space and has no potential energy, similar to how the bowling ball could just be rolling on the ground with no potential energy. I'm going to imagine now that this electron gets close to an atom, and you'll notice that I've added a few levels of negative energy to this atom. The electron encountering this atom is kind of like the bowling ball encountering a hole in the ground that looks something like this, with different levels of negative energy that the bowling ball can fall down. Right now, the electron is not in the atom, and in a similar way, the bowling ball is not in the hole. I'm going to bring them both close to the edge of the atom and the hole. Here, the electron is still free from the nucleus of the atom and is not affected by it. It requires 0 electron volts to escape the atom. In a similar way, the bowling ball is still free from the hole. It still has an energy of 0 joules, which means it's not actually in the hole yet. So both of these things are kind of at the boundary of these different energy levels, but haven't fallen into negative energy yet. If the electron gets closer to the nucleus, though, if it goes down into that negative 1.6 electron volt level, suddenly the electron is stuck orbiting the atom, and it would need 1.6 electron volts added to it to escape the atom. So this is exactly like the bowling ball falling into that first level of the hole, and suddenly the bowling ball would need 1.6 joules of energy to escape the hole. So that's what these negative energies of the atom and the hole mean. There's another comparison between these where they're both being held there by a force. The electron is being attracted to the atom by the electrostatic force, and the bowling ball is being prevented from leaving by the force of gravity. If no energy is added to these objects, the bowling ball is just going to remain in that hole, and the electron is going to remain in orbit at that level around the nucleus. So the energy that an electron has in an atom is always recorded as negative because it's telling you exactly how much energy is required to escape the atom. We can imagine the electron drops more and the bowling ball drops more. So here the electron would need 2.5 electron volts to escape the atom. And you can see the bowling ball would now require 2.5 joules to escape the hole. And here the electron would require 3.9 electron volts to escape the atom, just like the bowling ball would require 3.9 joules to escape the hole. So that is what these negative energies are communicating to you, and so we always record electron energy levels as negative in an atom. It's a way of recording that the electron is stuck in the atom and requires that much energy to escape. We can now cover some basic vocab for electron energy levels. First of all, an electron energy level itself, or an energy state, is an amount of negative energy any electron can have in an atom. So as an example, I would say that there are 3 energy levels in this atom. The ground level or ground state of an electron is the largest magnitude of negative energy an electron can have in an atom. Here I would say that the ground state of this atom is negative 3.9 electron volts. That's the lowest possible energy the electron can have, the farthest it can be from zero in the negative direction. We say an electron is excited when it is not in the ground state. Excited is also used as a verb to mean moving up energy levels. So as an example, if the electron went from the negative 3.9 to the negative 2.5 energy level, we could say something like it was excited to the second energy level. There are also 2 variables that I need to introduce. The letter n is the number of the energy level. The ground level is always called n equals 1, the next level up is always n equals 2, and so on. So this is how I would label that here. I know that negative 3.9 electron volts is my ground level, and as I go up, these are the other energy levels of the atom. E subscript n is the value of the energy at energy level n. So here I would say that E1 is negative 3.9 electron volts, E2 is negative 2.5, and E3 is negative 1.6. As a note, we normally don't call 0 electron volts an energy level of an atom because by the time an electron is there, it's no longer in the atom. I'll talk about this a little bit more at the very end of the video. A really fundamental fact about electrons and atoms is that electrons cannot exist between energy levels in an atom. We say that the energy of an electron is quantized because it can only exist in certain specific quantities and not between those quantities in the atom. So as an example, here the electron is existing at an energy of negative 3.9 electron volts, and that's okay because that's one of the energy levels of the atom. It could also exist here at negative 2.5 electron volts, but there's no physical way for it to exist anywhere between those energy levels. So if I tried to say that this electron had an energy of negative 3 electron volts, that would not work. That would not be physically possible because that's between energy levels of the atom. So we say that the energy levels of an electron are quantized because they can only come in very specific quantities. This idea of quantized energy is going to be important for the rest of this topic. Electrons cannot exist between specific energy levels in an atom. There's a limited number of values of energies they can have when they're in the atom. Because we don't want to physically draw a picture of every complete atom, to represent electron energy levels, we draw horizontal lines separated vertically by distance proportional to the energy difference between them, with the ground state on the bottom. As an example, this is one way I could represent this atom using a simpler diagram. This is the type of diagram that we usually use in these problems. You can see that the ground state is on the bottom, the other energy levels are above the ground state, and the distance between the lines is proportional to the difference between the energies. So the difference between negative 3.9 and negative 2.5 is 1.4, and 1.4 is larger than that other difference of 0.9 electron volts. So I drew line 1 and 2 farther away from each other than line 2 and 3 to represent that the energy difference between the first two is bigger than the second two. We're now ready to learn about the relationship between photons and electrons. So energy is conserved. This means it cannot be created or destroyed, which means that if an object loses energy, that energy has to go somewhere. It can't just disappear into nothingness. If an object gains energy, that energy also has to come from somewhere. And we know from a previous lecture, which I've linked in the description, that photons carry energy. So this is the relationship between photons and electrons. Whenever an electron loses energy, a photon is created with the exact amount of energy that the electron lost. Whenever an electron gains energy, a photon with that amount of energy is absorbed or destroyed by the atom. What this is telling us is that if this electron with an energy of negative 1.6 electron volts were to drop to an energy of negative 3.9 electron volts, I can see that the change in energy there is negative 2.3 electron volts. The electron would lose 2.3 electron volts of energy, but that energy has to go somewhere. It can't just disappear. And so if the electron is losing 2.3 electron volts, that means that as it does that, a photon is going to be created with exactly 2.3 electron volts of energy, and the photon leaves the atom and goes off in a random direction. So every single time an electron loses energy, that energy leaves the atom as a photon. The only way for the electron to gain energy, as an example, if we want to move it from negative 3.9 eV to negative 2.5 eV, I can see that the difference between between those energies is positive 1.4 electron volts. So that energy can't just magically appear, it needs to come from a photon specifically, and it needs to come from a photon carrying 1.4 electron volts of energy. If a photon impacts this atom with that exact amount of energy, the atom will absorb it, and the electron will move up that energy level. If a photon does not have the exact energy required to get an electron to a different energy level, it passes through the atom, because the electron cannot exist between energy levels. For example, if a photon impacted this atom carrying 0.5 electron volts, right now our electron is at negative 2.5 electron volts of energy. That additional 0.5 electron volts would be enough to get it to negative 2 electron volts, which exists between energy levels. And we know that the electron cannot exist between energy levels, that's not allowed. What that means is that the photon will not be absorbed by the atom, because if it were absorbed, the electron would do something that's impossible. What happens instead is that the photon just passes right through the atom and continues moving. That's going to be another really fundamental concept that we'll come back to a lot in this topic. Because electron energy is quantized, the electron can only be at specific energy levels, there are a limited number of energy changes an electron in an atom can go through. Because every change in energy emits or absorbs a photon, there are a limited number of photons which can be emitted or absorbed. So every energy change involves a photon with that same amount of energy, and there are a limited number of energy changes that can happen, so there are a limited number of photons that can interact with this atom. We can find each possible photon's energy using the electron energy levels. Normally when we do these problems, we're given energy levels that don't include the zero energy level, so I'm going to ignore that for now. And I'm going to use this chart to understand all the different ways an electron's energy can change in this atom. I'm going to start by finding the possible energies of photons that this atom could emit specifically. I'll worry about absorbing photons later. When an electron emits a photon, that's when it's moving down in energy level. So I just need to find all the different ways that an electron could move down in energy level in this atom. I can see as an example that it could follow this path where it drops negative 0.9 electron volts. If it follows that path, a photon of 0.9 electron volts is created, so that's one of the possibly emitted photons from this atom. The electron could also follow this path and drop 1.4 electron volts, which would mean that a photon would be created of 1.4 electron volts. So that's another possible emitted photon from this atom. There's one more possible path this electron could take where it drops straight from the third level to the first level. If it took this path, I can see that the energy change would be negative 2.3 electron volts. So that would mean a photon of 2.3 electron volts would be emitted. These are the only possible ways that the energy of an electron can change in this atom. There are no other paths it can take because it can't exist between energy levels. It has to end at one of the energy levels. So these are the only ways that an electron can lose energy if it exists in this atom. And so my list of possible energies of emitted photons are the only possible photons that can be emitted by this atom. This atom can only emit a 0.9, a 1.4, and a 2.3 electron volt photon, and no other energies of photons can be emitted. We can now think about which photons could possibly be absorbed by this atom. Those would be the energy changes of an electron as it went up in energy, because photons being absorbed add energy to the electron. And if you think about it, the possible ways that an electron can gain energy here are actually just going to be the reverse of the possible ways that it can lose energy. If I change the direction of all of these paths to go up in energy instead of down, I can see that the possible energy gains by the electron are the exact same as the possible energy losses by the electron. So this means that the possible energies of emitted photons always equal the possible energies of absorbed photons, because there are only three ways this electron can gain energy, and each one is the exact same amount of energy that it can emit. If I want my electron to gain 2.3 electron volts, it would have to absorb a photon of 2.3 electron volts, which is one of the three possible emitted photons. And if I wanted to gain 1.4 electron volts, it would have to absorb a photon of 1.4 electron volts, which is another emitted photon. And if I wanted it to gain 0.9 electron volts, it would have to absorb a photon of 0.9 electron volts. So this will always be true. The possible energies of emitted photons in an atom are always equal to the possible energies of absorbed photons. The last thing to know before we start doing example problems is that we can use an electron energy level diagram to find all possible energies of emitted and absorbed photons. Because we can use a photon's energy to find its wavelength and frequency, this is something I talked about in the previous lecture, which I've linked in the description. We can also find all the possible wavelengths and frequencies of the emitted and absorbed photons. I'll give you an example of doing that here. I can see I have 4 energy levels. That axis on the left is just telling me that's measuring energy in electron volts. And I can find either all the ways that an electron can emit or absorb a photon. I'll find all the ways that it can emit a photon, which means going down in energy. So I just need to use this chart to find all the different ways that an electron could lose energy in this atom. The first way would just be going from the highest to the lowest energy like this. And I can see that that energy difference is negative 12.75 electron volts. So if an electron did that, it would produce a photon of 12.75 electron volts. So that's the first possible photon that could be emitted. This is another energy change that could happen. I can see that's 1.55 electron volts. So I can just keep going through and finding every possible drop in energy that can occur on this chart and record the energy change for each one, and that's going to be the energy of an emitted photon. There's one here, and here, and here. Those are all the possible energy drops. So that means there are 6 possible energies of photons that this atom can emit, and I just found all of them and listed them on this table. I can use these energies to find the frequency of each photon using the equation for frequency and energy of photons. Energy equals Planck's constant times frequency. If I rearrange for frequency, I get this. And then I just need to plug in my numbers, remembering that I need to convert from electron volts to joules. So when I do that and plug in energy, I get a frequency for that first photon of 3.08 times 10 to the 15th hertz. And I can follow the same process for the others. If you have the frequencies already, there are actually 2 ways you can find the wavelengths of photons. You can either use the wavelength equation that uses the Planck constant, and if you did that, you would get this value. You can also use the fact that the speed of light is equal to its wavelength times frequency. So since you already have the frequency, you could also just divide the speed of light times the frequency to find the wavelength. So that would be the wavelength of the first photon, and these are the other wavelengths. So this is cool. I'm now able to find the wavelength and frequencies of light that will be emitted by an atom. These are all the possible wavelengths and frequencies of light that the atom will emit based on its specific energy levels. Finding these wavelengths and frequencies will be extremely important in the next lecture when we cover the absorption and emission spectra of atoms. Example number 2 asks 2 questions: a change between which 2 energy levels will emit a photon with the smallest possible wavelength, and which change will absorb a photon with the smallest possible frequency. You'll notice here that the energy levels are not written as numbers. It's just variables E1, E2, E3, and E4. So we can't just find all the wavelengths and frequencies and get the answer. We need another way of understanding this. In the lecture on photons that I've linked in the description, I talked about how the smaller the wavelength of a photon, the more energy it carries. So if I'm trying to find a photon with the smallest possible wavelength, that means I'm trying to find the photon with the largest possible energy that I can get from this atom. So I'm looking for the greatest possible energy change on this chart. And because the photon is being emitted, I'm looking for the greatest possible energy change down the energy levels. So if I want a photon with the smallest possible wavelength, it also has to have the greatest possible energy. So I'm looking for the greatest possible energy change down on this chart, which, if I think about it, would have to be here. There's no larger change in energy that can happen between these levels than going from E4 down to E1. And I know it's going down because we're emitting a photon, so the energy change that will produce the smallest possible wavelength is going from E4 to E1. That would be the answer to that first question. If we're looking for the smallest possible frequency, I remember from the photon lecture that the smaller the frequency, the smaller the energy. So I'm now looking for the smallest possible energy change that can happen on this chart. And I remember that the spaces between the horizontal lines tell me how large or small the energy change is. The larger the space, the larger the change. So if I'm looking for the smallest possible energy change, I'm looking for the smallest possible space between 2 lines. And because the photon is being absorbed, the electron will have to go up in energy, so that would be here. That's the smallest possible space between 2 lines on this chart. Going from energy level 3 to 4 will produce a photon with the smallest possible frequency that can be emitted by this atom. Example number 3 says a photon with energy of 2.1 electron volts is absorbed by this atom and excites an electron. The electron will move between which 2 energy levels? So I basically just need to look around at this chart and see if I can find which 2 lines have a difference of exactly 2.1 electron volts between them. And if I look around for that difference, I eventually find that it exists between 2.5 and 0.4. So that's where the electron would change by exactly positive 2.1 electron volts. So the answer to this would be moving from negative 2.5 electron volts to negative 0.4 electron volts, or between the second and fourth energy levels. There are times when you'll have to calculate the energy states of an atom using an equation. As an example, the equation for the energy levels of hydrogen atoms is E subscript n is equal to negative 13.6 over n squared electron volts. What is the wavelength of a photon required to excite an electron from the ground state to n equals 3? So to know the wavelength, I need the energy, and to know the energy change, I need to know the difference between the ground state and the third level. So I need to know what those energies are. I know that the ground state is just a code word for n equals 1. So to find the energy there, I just plug in 1 into n, and I find negative 13.6 electron volts. So that's the energy of the ground state. And the energy at the third level, I just plug in 3 into n, and I get an answer of negative 1.5 electron volts. If an electron is excited from the ground state to the third state, I can see that the change in energy is going to be positive 12.1 volts. So that's the required energy of a photon that needs to be absorbed to make that happen. So I now have all the information I need to solve for the wavelength of the photon. And I know that the energy is 12.1 electron volts. I just need to convert that to joules. And when I do that, I find it's 1.94 times 10 to the negative 18th joules. So I plug that into my equation and get a final wavelength of 1.03 times 10 to the negative 7th meters. So if I send a photon with that exact wavelength to impact the atom, the photon will be absorbed and excite an electron from the ground state to the third energy level. These are just a few extra notes before we go. IB doesn't cover these specifically, but they still might be useful to know. The energy levels of an electron always get closer together as they increase. You may have noticed that pattern throughout the video. Real atoms actually have infinite energy levels that get closer and closer and closer to zero. So they kind of asymptotically approach 0 electron volts. And there's always an infinite number of them as they get closer and closer to zero. So we sometimes refer to the 0 electron volt line as n equals infinity. It's the infinitieth possible energy level because there's always an infinite number of energy levels leading up to it. But in most idealized problems, we only worry about a few energy levels at a time. The very last thing to know is that all atoms of the same element have the exact same values for their energy levels. This will be really important in the next lecture on absorption and emission spectra. As an example, the energy levels of all hydrogen atoms follow this formula. The energy is equal to negative 13.6 over n squared electron volts. So that is everything that you need to know about the relationship between electron energy levels and photons. This lecture is going to be about absorption and emission spectra. I'm assuming in this lecture that you've seen the previous lecture on electron energy levels, and if you haven't, I've left a link to that in the video description. You will remember from that lecture that electrons exist at specific energy levels in atoms, and every single time an electron goes down in energy level, it emits a photon of that exact same amount of energy. So just observing this electron here, I can see that every time it drops a certain amount of energy in electron volts, it emits a photon of the same energy. And if we want to increase an electron's energy in an atom, we have to add a photon to it, where the photon is absorbed by the atom, and the photon has to have that exact amount of energy required to get the electron to the correct energy level, because electrons cannot exist between energy levels. In another lecture on photons, which I've also linked in the description, I talked about how if we know the energy of a photon, we can also automatically know its wavelength using this equation. Before I use that equation, I just need to convert the energy to joules, so when I do that, this is what I get. So I can find the wavelengths of each of these three emitted and absorbed photons, and these are what I find them to be. So these are the wavelengths of photons which can be absorbed or emitted by this atom. And if a photon that doesn't have one of those exact wavelengths interacts with this atom, what's going to happen is the photon is just going to move straight through the atom without affecting it, and without being absorbed by it. That's going to be a really important concept here. This is all review. We covered this in the previous lecture, but this is going to be really central to this lecture about spectra. I'm going to say that we have a source of white light and some kind of detector that can detect all the different wavelengths of light that are impacting it. And white light actually contains all possible wavelengths of photons. So if we shine this white light on this detector that can detect which wavelengths are present, this is what it would look like. The detector would record every possible wavelength of light as being present because white light contains all possible wavelengths. And in this detector, we can imagine we order the wavelengths from smallest to largest, going from left to right. I'm going to shine that light on this detector again, but this time I'm going to pass it through the element that we were looking at in the opening of this video. So that element is now between the white light and the detector. So what would the detector detect now? Well, every possible wavelength of light would come out of the white light source and begin to fill up our detector with all the possible wavelengths of light. But I know there are a few wavelengths that this atom can absorb. So what happens when one of those wavelengths interacts with the atom? Because again, white light contains every possible wavelength, so it also contains those 3 wavelengths. If that wavelength of 5.4 times 10 to the negative 7th meters appeared, the atom could absorb this photon and it would become electron energy. So when that happens, the photon does not reach the detector. So there's going to be one very small part of our chart of wavelengths that's going to be just a black line, because no light was detected at that wavelength because the light was kind of eaten up by the atom before it got to the detector. And if we're ordering this light by the wavelength, that black line would appear right at 5.4 times 10 to the negative 7th meters, because that was the wavelength absorbed by the atom. We can now observe the other wavelengths. Other wavelengths would continue to pass through the atom. But when we hit the next wavelength that the atom could absorb, that wavelength would also be absorbed into the energy of one of the electrons. And so again, a black vertical line would appear at that exact wavelength of 8.9 times 10 to the negative 7th meters. More light would pass through. And finally, there would be one more black line because this wavelength of 1.4 times 10 to the negative 6 meters would also be absorbed by the atom. Finally, photons of very long wavelength would pass through and complete the chart. So we call this an absorption spectrum. An absorption spectrum shows the spectrum of electromagnetic wavelengths pass through a substance, a collection of atoms, with dark lines due to the absorption of specific wavelengths. So if I had a large amount of atoms of this substance, and I passed electromagnetic waves of every possible wavelength through the substance, and measured which wavelengths came out the other side, almost all wavelengths would make it through the substance, but there would be a few very specific wavelengths that would not make it through, that would cause black lines to appear on my diagram. I would call this diagram an absorption spectrum for this specific atom. We can now imagine that we have atoms of the same element, and this time we can place them in total darkness, and see if we can measure any of the photons being emitted by the element. So I know that if electrons in this element were to lose energy, they could emit a photon of 5.4 times 10 to the negative 7th meters, and a photon of 8.9 times 10 to the negative 7th meters, and a photon of 1.4 times 10 to the negative 6th meters. So those would be the 3 places on my chart where I would detect photons. Everything else would be black. There wouldn't be any other EM waves hitting this chart. So we would call this an emission spectrum because this shows the spectrum of electromagnetic wavelengths emitted by a substance, with bright lines due to the emission of specific wavelengths. You can see that the places where the lines show up on an absorption or an emission spectrum are the wavelengths of photons which the substance can absorb or emit. In the last lecture, we learned how to find the energy, frequency, and wavelength of any photon that an atom can absorb or emit. And here you can see that these spectra diagrams show us those wavelengths that the atom can absorb or emit, physically showing up on a chart we can make of all possible electromagnetic waves passing through or emitted from the substance. Because all atoms of the same element have the same energy levels, they absorb and emit the same photons, and so they produce the same absorption and emission spectra. So as an example, all hydrogen atoms have these energy levels that I've listed here. I can run through and find all the possible energies of the photons that could be absorbed or emitted by a hydrogen atom, and I'll use the equation to find the wavelength. This is what I get when I do that. So if I fill in an absorption or emission spectrum using these wavelengths, it's going to look something like this. This is not drawn exactly to scale. But because all hydrogen atoms have the exact same energy levels, they all have the same possible energy changes, which means they all emit or absorb the exact same photons with the same energies and the same wavelengths. So every single time you make an absorption or emission spectrum of a hydrogen atom, it's always going to look exactly the same, something like this, with the wavelengths in the exact same spots. The spectrum of an element is like a fingerprint that we can use to identify which elements light has passed through or been emitted from. As an example, these are the emission spectra of different common elements. I'm just going to roll through, and you can see how each one is kind of like a fingerprint for that element. We can always identify which element we're seeing in an emission spectrum because we already know what that element's spectrum looks like. So if we're given an emission spectrum, we can just match it up with the correct element. This is actually how we know which elements exist in stars. We look at the light from stars and see which wavelengths are missing, and then match the missing wavelengths to the spectra of elements. So this is how we know the chemical composition of the entire universe. You can see in the picture that I've posted that this is the sun's absorption spectrum. And you have all these different fingerprints of elements kind of superimposed on top of each other, and we can just pick up the individual patterns and say, okay, This set of wavelengths is produced by hydrogen, this is produced by iron, by calcium, by magnesium, etc. So this is how we know the exact chemical composition of the sun and all stars that exist in the universe. This next idea is really central to the topic. This gets asked about a lot on tests. Absorption and emission spectra are evidence for the fact that electron energy levels are quantized. We can understand why by asking what the spectra would look like if electron energy were not quantized. This would mean that instead of existing at very specific energy levels, electrons could exist at any level of energy around the nucleus. It's difficult to say exactly what would happen here because we would live in a very different universe if this were true. But one thing that would happen is because the electrons are able to exist at any energy level, they can now absorb any wavelength of photon. So any and all wavelengths could be absorbed by these electrons. So it could be that the spectra would just be black all the time. It could also be that maybe after reaching a certain limit of energy intake, and maybe when all the electrons have escaped the nucleus because they've gained so much energy, whatever photons just happen to randomly be left could pass through the nucleus and pop up as random lines on our chart. I would imagine that if the same thing happened again, because those wavelengths are random, this would result in different wavelength readings on the chart. So instead of getting the same fingerprint every time for each element, we would get just random lines in random positions. This is probably not what would actually happen, and it's probably just a matter of time before a professional physicist hops into the comments and tells me that I am wrong and something different would happen. But we don't live in that universe, so that doesn't really matter so much. What does matter is that the one thing that would not happen if energy levels weren't quantized is the exact same absorption and emission lines showing up for every single atom of the same element. The fact that all atoms of the same element always show the exact same spectra pattern means that the photon energies the electrons can emit or absorb are always exactly the same. Because if it's always the same wavelength that's absorbed, it's always the same photon energy that's absorbed. And this means that the electrons can only experience very specific energy changes, which means their energy must only exist in specific quantities and cannot exist between those quantities. So again, if we have the same spectra for all atoms of the same element, that implies that the same wavelengths of photons are absorbed by every single atom of the same element, which means the same energy of photons is absorbed, which means the electrons in each atom of the same element can only change energy by the same specific amounts, which means that the electron energy is quantized. It can only exist in these very specific amounts and cannot exist between them. If it could exist between them, then we would get additional wavelengths that were absorbed or emitted. And that's not what we see in the real world. We always see the exact same spectra patterns for all atoms of the same element. So this is how we know that electron energy is quantized. So absorption and emission spectra are evidence that electron energy is quantized. Just a few important notes to finish up the lecture. The way absorption and emission spectra are drawn mistakenly implies that they only detect wavelengths on the visible spectrum from visible violet to red light. They're very often drawn as rainbows, like what I've drawn here, which implies that they only deal with visible light, but absorption and emission spectra actually measure the full electromagnetic spectrum, so they can measure any wavelength or frequency of photon. And remember, visible optical light is only one very small part of the much larger electromagnetic spectrum. Because all photons with the same wavelength also have the same frequency, we can also draw absorption and emission spectra with frequency instead of wavelength. So because the speed of light is equal to wavelength times frequency, I can use this equation to solve for the frequency along with the fact that this is the speed of light. So if I wanted to convert this into a frequency diagram, this is what it would look like. I just replaced all the wavelengths with frequencies instead. So we're also totally allowed to draw spectra with frequency instead of wavelength. This final note is hyperspecific, but each energy change only occurs between two specific levels in an atom and doesn't occur twice in the same atom. This means that each line on an absorption or emission spectrum is associated with two specific energy levels of the electron and only those two. So as an example, these are 6 of the energy changes for hydrogen, and each of these energy changes only appears once. As an example, there's never going to be another change between two energy levels in hydrogen that's equal to 10.2 electron volts. That's just never going to happen. So that specific wavelength on the spectrum is associated specifically with a change from the n equals 1 to n equals 2 or vice versa level of electron energy. So each individual line on the spectrum only represents a change in energy between two very specific levels. You can see that the purple line is from n equals 1 to n equals 4, the orange line is from n equals 2 to n equals 3, and there will never ever be a situation on a spectrum where one line goes with two different pairs of energy levels. Like the orange line could never possibly be associated with like n equals 5 to n equals 8 as an example. It can only be associated with one pair of levels because each individual energy change only occurs once in an atom's energy levels. And that's everything that you need to know about absorption and emission spectra. This lecture is about the Geiger-Marsden experiment, which was an experiment carried out in 1911 to determine the structure of atoms. The experiment disproved the plum pudding model of an atom, which we'll talk about in a moment, and showed that atoms have a very small, dense, positively charged nucleus and are otherwise mostly empty space with some electrons floating around. The scientists performing the experiment shot alpha particles at a piece of gold foil and observed the directions that the particles scattered. This is also sometimes called the Rutherford Geiger-Marsden experiment, since Rutherford directed the experiment while Geiger and Marsden carried it out. Before the Geiger-Marsden experiment, scientists believed in something called the plum pudding model of an atom. They knew that there were positive and negative charges in an atom, and in non-ionized atoms the charges added together to make zero, but the plum pudding model of an atom said that an atom was small electrons embedded inside of a uniform positively charged mass, something like this picture right here, where you have electrons stuck in a spherical, low-density, positively charged mass. The reason it's called the plum pudding model is that this physically looks like a plum pudding, with little pieces of fruit embedded in the cake. And the Geiger-Marsden experiment allowed us to move from this model to a more correct model of an atom, called the nuclear model, where the positive charge of an atom exists in a very small dense nucleus surrounded mostly by empty space and electrons. So the experiment showed that the plum pudding model was probably not correct, and hinted at the nuclear model instead. In the experiment itself, scientists took a very thin film of gold foil and placed it inside of a circular screen. This is an overhead view of the experiment. I want you to imagine that when you're looking at this, you're looking physically down at a table that you're standing over, and the circular gray screen is resting on the table horizontally, and the gold foil is placed in the middle. The reason why the scientists used gold specifically is that gold can hold its structure while still being incredibly thin. The scientists doing the experiment were pretty confident that the gold foil itself was actually probably only 2 or 3 lines of atoms thick. So any interference with these atoms would be the result of interference with just a single atom, or maybe 2 atoms at the most. So they knew that whatever happened in the experiment would be the result of interference with just a single atom, rather than the result of the interference of very large amounts of atoms. Because there could be other factors there affecting the experiment that we didn't know about, but if they only dealt with individual atoms, they could get a pretty clear idea of the shape of the atom. Scientists set up a source of alpha radiation, just a radioactive substance, inside of a lead box, and they created a very small opening in the box, and the substance would emit alpha particles in every direction, but the only alpha particles that could actually escape the box would have to be going straight through that hole, so they would continue along their same path and eventually go straight at the gold foil. Without the gold foil there, they knew that what would happen is an alpha particle would be emitted, hit the screen, and they would be able to see on the screen exactly where the alpha particle impacted the screen. There would be a little mark on the screen that appeared. So I'll use a green dot to represent what those marks look like. We now know that alpha particles are 2 protons and 2 neutrons, so they're positively charged. At the time of the experiment, it was known that the alpha particle is small, dense, and positively charged, but scientists did not yet know that it's a proton and a neutron because they didn't even know that protons and neutrons existed at the time. So they were trying to confirm the plum pudding model of the atom. And if the plum pudding model were true, one of 2 things would happen when you sent a lot of alpha particles through an atom. One possibility is that all the alpha particles would move through the atom. Because scientists assumed that the atom was very low density, the alpha particles could probably just effortlessly move through to the other side, because they were much smaller and denser. The important thing here, though, is that the plum pudding model predicted that the atom was uniform. There's no small, dense nucleus in the center surrounded by empty space. Instead, the entire atom is just the same low-density object. And so no matter what part of the atom a particle moves through, the top, middle, and bottom paths that the alpha particles took should all be the same going through the atom, regardless of which specific part of the atom they traveled through. The other possibility was that maybe the atom was actually denser than alpha particles, or dense enough for them to be repelled. So maybe all the alpha particles would be repelled back this way. This wasn't a serious assumption, but it was obviously a possibility in the plum pudding model as well. Because if the model is true, there's a uniform density, so wherever the alpha particle impacted the atom shouldn't matter. Same density everywhere, so it should always bounce off, or it should always go through. So if the plum pudding model were true, we would expect one of these behaviors or the other. And it was known that the alpha particles were small and dense, and that the atoms were much larger and less dense, so it was assumed that the top example would happen.
So based on those assumptions, this is what we would expect to see if the plum pudding model were true. If we shot a lot of alpha particles at the gold foil, we would expect their imprints on the screen to appear here. The reason why we would expect them to see them here is that if all the alpha particles were able to effortlessly move through the atom, we would expect that all the alpha particles would follow this path through the gold foil, because the gold foil is just made of individual atoms. So we would expect them to appear there on the other side of the foil. The other possibility, if the atom were more dense, is that this pattern would appear. Because if the atom were more dense, all of the alpha particles would be rebounded off of the atoms in random directions, and so the alpha particles sent here would follow this pattern here and impact the other side of the screen in random spots. So we would expect one or the other pattern if the plum pudding model were true, but that's not what actually happened. Instead, we got this pattern here. You can see that most of the alpha particles did hit the other side, but there are a few that are off in strange directions and a few that actually bounced off the gold foil and exist on the left side of the gold foil. This hints at a pattern of the alpha particles moving through the atom like this, because when they came out of the source of the radiation, most of them moved straight through the gold foil, but a few bounced off in random directions, and a few were even bounced backwards in the opposite direction like that. So a majority moved through, but you had a few that bounced off in other directions. So if you look up at my diagram of the atom, what this implies is that most of the atom is very easy for particles to move through, but there must be some very small, very dense spot where alpha particles are bounced off that deflects alpha particles and pushes them away. And it's dense enough for alpha particles not to just effortlessly move through it. It was known that alpha particles were positively charged, so it was assumed that the small dense nucleus repelling them must also be positively charged. So this pattern hinted that the plum pudding model was wrong, and instead a nuclear model of the atom was correct, where most of the atom was empty space that was very easy for alpha particles to move through, but a very small portion of the atom must be a small, dense, positively charged region that repels alpha particles. So this is how we got from the plum pudding model of the atom to the nuclear model of an atom. And that's how the Geiger-Marsden experiment helped us progress from one to the other. This video is about the 4 fundamental forces in physics, and I want to note super quick that this entire series on particle physics that I'm doing is only going to cover the material that IB physics students specifically are expected to know. There is so much that you can say about particle physics and so much you can say about the 4 fundamental forces, but this video will only cover what you're expected to know as an IB physics student specifically. So the 4 fundamental forces are gravity, the weak nuclear force, the electromagnetic force, and the strong nuclear force. We've encountered some of these forces before, like obviously we've worked with gravity and the electromagnetic force, but we haven't worked with the weak and strong nuclear force so much. I have a few facts about the forces that you'll need to memorize. First of all, you can see I have them ordered from relative strength, where gravity is the weakest force and the strong nuclear force is the strongest force. We say that gravity is the weakest force because it requires just so much mass to create even an average-sized force of gravity. Whereas for the electromagnetic force, it doesn't require an especially large amount of charged mass in order to create a very large electric or magnetic force. So we say the electromagnetic force is stronger than the force of gravity. The range of gravity and the electromagnetic force is infinite. 2 objects at any distance can put a force of gravity on each other or an electromagnetic force on each other, but you can see the weak and strong nuclear force cut off after very short amounts of distance. Gravity acts on all objects with mass, and we know the electromagnetic force acts on all objects with charge. The weak nuclear force acts on very specific parts of an atom, specifically leptons and quarks, and hadrons, because hadrons are made of quarks, and protons and neutrons are hadrons, so the weak force also acts on them. And the strong nuclear force acts on quarks, but not leptons. I've also listed the role that each force plays in the universe. Gravity holds things like stars, planets, solar systems, and galaxies together, and also obviously keeps us on Earth. The weak nuclear force is responsible for radioactive decay, specifically beta decay, which we'll talk about a lot, and neutrino interactions. The electromagnetic force attracts and repels electrically charged and magnetized objects, and it holds electrons in orbitals around atoms. And the strong nuclear force holds nucleons together. Otherwise, protons would be pushed apart by the electromagnetic force. The reason we call these the 4 fundamental forces is that all other forces in the universe that we experience are actually just one of these 4. In fact, basically every force you experience in everyday life that isn't gravity is the electromagnetic force, which is a little surprising, but it actually makes sense when you consider that all objects are made of atoms. For example, if we have an apple,
supported by the ground is applying a normal force up on the apple. So in previous units on force, we referred to that force as the normal force. But if you zoom up to the atomic level of the atom, what's actually happening here is that if you zoom up very close on how the apple is interacting with the floor, like on the atomic level, you would see that what's actually happening is that the electrons in the apple are actually repelling the electrons in the ground because they're both negatively charged. So the electrons in the apple are pushed up, the electrons in the ground are pushed down, and so the whole mass of the apple is pushed up. So those atoms experiencing the electromagnetic force is actually what causes the normal force to exist. So the normal force is actually just the result of the electromagnetic force occurring between particles in the atoms. One interesting implication of this is that the electrons in the atoms never actually physically make contact with each other. What we humans experience as physical contact between objects is actually just electrons repelling each other, and those electrons are never actually physically touching each other. They're being repelled by the electromagnetic force before they make contact with each other. I have separate video lectures on gravity and the electromagnetic force, which I've linked in the description, so the rest of this video will focus on the weak and strong nuclear force specifically. In other lectures linked in the description, I discuss the exchange particles or bosons which mediate the 4 fundamental forces in particle physics. The rest of this lecture will just explain the basics of the weak and strong nuclear force. IB Physics also expects you to know something about exchange particles and bosons. In other lectures linked in the description, I discuss what these are and how they're related to the 4 fundamental forces in particle physics. But to cover those, I need to cover other aspects of particles, so this lecture will just explain the basics of the weak and strong nuclear force. The weak nuclear force causes nuclear decay. For example, it's the force that causes a neutron to emit an electron and antineutrino and become a proton. In IB Physics, we'll mainly be worried about the weak force in the context of beta decay. So you'll remember that a neutron emitting an electron and antineutrino is actually an example of beta decay. What's actually happening here is that if you open up a neutron and see what's inside, you would find that it's actually made of 3 smaller particles called quarks, which we'll talk about in the next lecture. And what happens in the beta decay of a neutron is that one of the down quarks specifically releases an electron. And the force that causes that electron to be expelled from the quark is the weak nuclear force. And the weak nuclear force is also causing an antineutrino to be emitted. And because these are interacting with the quark also experiences a weak nuclear force in the opposite direction due to Newton's third law. So these particles are expelled and the down quark becomes an up quark. And when you have 2 up quarks and a down quark, that actually causes the particle to become a proton instead of a neutron. So that was an example of beta decay, and you can see that the weak nuclear force was responsible for that. It was responsible for those particles being expelled from the quark. So the weak force acts on leptons and quarks, and hadrons because hadrons are made of quarks. Protons and neutrons are hadrons, so the weak force acts on them. So that's what you'll need to know about the weak nuclear force. The strong nuclear force holds nucleons in the nucleus. It prevents them from being pushed apart by the electromagnetic force. It acts on protons and neutrons, but does not act on electrons or other leptons. That's a really common test question. You have to remember that it acts on protons and neutrons, but not electrons. If the strong nuclear force didn't exist, the protons in the nucleus of an atom would just push each other apart with the electromagnetic force, because they're both positively charged, so they would just move away. So there's this other force in the nucleus resisting that pull of the electromagnetic force that we call the strong nuclear force, holding the nucleus together. The strong nuclear force doesn't only hold the nucleus together, but it also holds individual quarks in a hadron like a proton or neutron. So the strong nuclear force is also holding these in place. And a notable thing about the strong nuclear force is that if these start to separate, the strong nuclear force that they're putting on each other does not decrease as the quarks move away from each other. There's actually something special that happens called quark confinement, which this video doesn't really cover, but because of the increase in potential energy between these quarks, after a certain distance, if they continue to separate from each other, that energy will actually become new quarks that they'll pair with. So these quarks can never really escape being around other quarks. But we'll talk about that more in future lectures. So that's everything that you need to know about the 4 fundamental forces in physics. This lecture will be about nuclear radiation and decay. This will basically be an intro to the idea along with some vocabulary. So nuclear radiation and decay occur in unstable nuclei, which is where the strong nuclear force does not create enough binding energy to permanently hold the nucleus of an atom together. The nucleus will eventually break apart and lose some mass and/or energy and become more stable as a result. This graph shows the general relationship between the number of protons p, the number of neutrons n, and the stability of a nucleus. The farther a nucleus is from the line of stability, the more unstable it is. So I'll start with this purple line that represents where the number of neutrons is equal to the number of protons. So this red line here shows in general where the most stable atoms appear. So you can see it's not always the case that the most stable atoms have an equal number of protons and neutrons. After a certain number of protons to remain stable, atoms actually have to have larger and larger amounts of neutrons compared to protons. So that's what that upward curve of the graph represents. What that means is that beyond a certain number of protons, you need a greater number of neutrons than protons to have a stable nucleus. So the farther a nucleus is from this line of stability, the less stable it is. As an example, carbon-12 is stable because it has the same number of protons and neutrons. You can see it has 6 protons, and because its atomic mass is 12, that means it must have 6 neutrons to add together with the protons to make 12. So at the lower end of that graph, atoms are the most stable when they have an equal number of protons and neutrons. So carbon-12 is more stable than other isotopes of carbon, like carbon-14. You can see that carbon-14 has the same number of protons as carbon-12, but it has more neutrons. It has 8 neutrons instead of 6, and so it appears higher on the graph, and so it's farther away from the line of stability, and so we know it's less stable than carbon-12. Carbon has a small enough number of protons where it's most stable where the protons and neutrons are equal to each other. We can compare this to something like uranium with 92 protons. The most stable isotope of uranium is 238, which means it has 146 neutrons and only 92 protons. And you can see if we decrease the number of neutrons, if we go down the y-axis to uranium-235, that's actually less stable than uranium-238 because it's farther away from the line of stability. So uranium-238 has so many protons that actually bringing the protons and neutrons closer together actually makes it less stable. That's the general relationship between the number of protons, neutrons, and how stable the isotope is. These are more vocab words than you need to know. When an unstable nucleus loses matter and/or energy, we call the matter or energy it lost radiation. Radioactive decay is the name for the process of an atom losing mass and/or energy. And we call the atom or material left over after decay the daughter of the initial atom. As an example, you can see I have a nuclear equation here where uranium is decaying into thorium and emitting a helium atom. So this whole process is called radioactive decay. The particle emitted is called radiation, and the part that's left over is called the daughter. As a rule, nuclear radiation always makes a nucleus more stable than it was before radiation happened. Finally, we call a substance radioactive if its atoms are unstable and give off radiation. As an example, if this uranium atom undergoes decay, it's going to lose 2 protons and 2 neutrons. And if you think about it, if the number of protons and neutrons that it loses are equal to each other, it's going to move parallel to that purple line because that's where the protons and neutrons are equal to each other. So when it becomes thorium, you can see it's now closer to the line of stability than it was before. So that fits the rule that says nuclear radiation always makes a nucleus more stable than it was before. Another term you'll need to know is ionizing power. This is the ability of radiation to strip other atoms of electrons when it interacts with them. The more ionizing power radiation has, the more damage it can do to materials. Radiation with high ionizing power is especially dangerous to humans because it can damage our DNA molecules. Because DNA contains instructions for what our cells do, this ionization of DNA can lead to cancer and other problems. So this is the reason nuclear radiation is dangerous to humans. These are 2 important and, to me, extremely strange and mysterious parts of radiation. We say that radiation is random and spontaneous. It's random because it cannot be predicted which nucleus will decay, and it's spontaneous because it cannot be predicted when a nucleus will decay. And when I say random, I mean really fundamentally random. Even more random than something like rolling dice. The numbers that dice land on are random to humans, but not really random to the universe. Because if we imagine rewinding the universe and rolling the dice in the exact same way, with the exact same force at the exact same angle, we would imagine that they would land on the exact same number. But radiation is actually fundamentally random in a way that that's not. Because if we were to observe over time which atom decays, and then if we found a way to rewind the entire universe and reset all other conditions of the universe to be exactly the same, and started observing from the exact same situation that all matter in the universe was in before, we would actually find that it would be possible for a different atom to decay. So there's nothing written into the universe at all about which atom will decay. Similarly, it can't be predicted when a nucleus will decay. If we started this clock, it could decay very early. But if we rewound the universe and started all over again, it could decay much later or not at all. So that's your introduction to nuclear radiation and decay. This lecture is about alpha, beta, and gamma radiation. Alpha, beta, and gamma are three different particles that a radioactive nucleus can emit in order to become more stable. And alpha, beta, and gamma decay are each names for the process of emitting that specific particle. A lot of physics doesn't require much memorization, but this is one of the few areas that does. You're going to need to memorize all of the information that I've listed here about each type of particle. So we'll start with alpha particles and decay. Alpha particles have 2 neutrons and 2 protons and no electrons. This means they're helium nuclei with a +2 charge. The symbol for an alpha particle is the Greek letter alpha, and the charge is +2. Alpha particles have the highest ionizing power, which means they have the most ability to strip electrons off of other atoms. That means they're the most dangerous to humans because remember, the more ionizing power, the more capable the radiation is of damaging our DNA. They have low penetrating power, however. They can be stopped by something as thin as a tissue. So alpha decay is a name for what happens when an unstable nucleus emits an alpha particle. Its atomic number decreases by 2, its nucleon number decreases by 4, and its charge decreases by 2. So I've written the nuclear equation for what happens during alpha decay. You can see, just like I said, the proton number decreases by 2, the nucleon number decreases by 4, and the charge decreases by 2, and you're also left with this additional alpha particle. As a reminder, nuclear decay always makes a nucleus more stable, so if an atom has too many protons, alpha decay occurs and reduces both the proton and neutron number by 2. So alpha decay really only happens with larger nuclei. I talked about this line of stability graph in my separate lecture on radioactive decay, which I've linked in the description. So assuming you already know what this means, alpha decay is most likely to occur anywhere between the purple line and the curve of the red line. Because what happens with alpha decay is it decreases the neutron number by 2 and the proton number by 2. So you can see that if you're in that general area between the purple and the red, and you decrease by that amount, you basically follow the purple line and get closer to the line of stability. Radiation always makes nuclei more stable, so that's specifically where alpha decay occurs, when there are too many protons compared to neutrons, and so the particle loses an equal number of both. A place where alpha decay wouldn't occur is when there are too many neutrons compared to protons. Because if the same thing happened and the neutrons decreased by 2 and the protons decreased by 2, you can see that alpha decay would actually bring the element farther away from the line of stability, which doesn't really happen in radioactive decay. Radioactive decay always brings the atom closer to the line of stability instead of farther away. So alpha decay basically won't happen anywhere above that red line. We can do a few example problems with alpha decay. For all radiation problems, you will absolutely never be expected to have the periodic table memorized. You're not going to be given the table on the IB test. And so all these problems can be solved without a periodic table. You just need to remember that the number of protons and neutrons is conserved on each side of the equation. So as an example, one thing that you will have to have memorized is that the alpha particle has 4 nucleons in total. And I know that the total nucleon number has to be the same on each side of my nuclear equation. So I know that 226 is equal to x plus 4. So I can see that the nucleon number for that other element is 222. That's about as complex as alpha decay problems get in IB physics. You just need to remember that an alpha particle has 4 nucleons and 2 protons, and that each side of a nuclear equation has to be balanced. Example problem 2 says when an alpha particle collides with a nucleus of nitrogen-14, a nucleus X can be produced together with a proton. What is the atomic number and nuclear mass of X? So again, I just need to remember that the equations are always balanced on each side. The nucleon number has to be equal on each side. So I can see that X is going to have 17 nucleons. And the proton numbers also have to be balanced. So I can see here that X would have 8 protons. So as long as you know what an alpha particle is, it's pretty easy to solve problems with it. A beta particle is an electron or a positron, which is an antimatter particle that has the same mass as an electron but positively charged. Technically the mass is negative because it's antimatter. We'll talk about that more in a little while. The symbol is the Greek letter beta, which looks a lot like a bee with a long tail, and then a minus or a plus sign next to it to symbolize the charge, whether it's an electron or a positron. Beta particles have medium ionizing power, so they're not quite as dangerous as alpha particles to humans, but they also have more penetrating power. They can be stopped by something like aluminum. Beta decay is a little strange. One of two things happen. A neutron emits an electron and antineutrino and becomes a proton, or a proton emits a positron and neutrino and becomes a neutron. You're going to have to remember that neutrinos are associated with beta decay. They're their own separate particles. You can see that I've listed their symbols on the bottom left. And I also have the equations for beta minus and beta plus decay on the top of the screen. So beta decay occurs if an atom has too many protons or neutrons. It causes the number of protons and neutrons to become more balanced. Beta minus decay happens when there are too many neutrons. It changes a neutron into a proton. And beta plus decay happens when there are too many protons. It changes a proton into a neutron. So beta minus decay can happen anywhere above and to the left of the red line, and beta plus decay can happen anywhere below and to the right of the red line. Just to visualize this a bit more, if we imagine we have an element up here, beta minus decay causes it to lose a neutron and gain a proton. So you can see it would move this way along the graph, which brings it closer to the line of stability. And that's what nuclear radiation does. It makes the nucleus more stable than it was before. So that's why beta minus decay occurs above and to the left of the red line. And beta plus decay adds a neutron and takes away a proton. So it would move the nucleus up like this, which again you can see is moving toward the red line. So that's why beta plus decay happens below and to the right of the red line. There are two correct ways to write beta particles in equations, either as lowercase e or as beta, because they're both electrons and positrons. There's one really weird aspect of this notation that only comes up in beta radiation problems. We write the electron or beta particles as having proton numbers of -1 and +1 when doing beta decay problems. Obviously, they don't actually have these values. They don't have protons moving along with them. The numbers are there to balance the nuclear equations for beta decay. So this is just a way of saying that if an electron were emitted, you should expect a proton to appear somewhere else that didn't appear before, while the nucleon number remains the same, which is what beta decay does. I'll show you how this is used in a few equations. A nuclide of the isotope potassium-40, which you can see has 19 protons, decays into a stable nuclide of the isotope argon-40, which has 18 protons. Identify the particles x and y in the nuclear equation below. So I'm going to start by figuring out what the values are for x. I know automatically that this is beta decay and not alpha decay because the atomic mass is not changing. So beta decay keeps the nucleon number the same. So that's a way that you can distinguish between alpha and beta decay. Alpha decay reduces the nucleon number by 4. Beta decay keeps it exactly the same. For x, I know that the proton numbers have to balance. So I can see that x's proton number is +1. And I can see from my equation on the top that this goes with a beta positive particle, or a positron. So I know that x specifically is a positron, so I would record it like this in my answer. And I know that if a positron is emitted, according to my equations, a neutrino is also emitted. So that means that y has to be a neutrino and not an antineutrino. Beta decay is complicated in that way. You have to have it memorized that when you have a positron, you'll also have a neutrino, and when you have an electron, you'll have an antineutrino. These equations are not given in your IB data booklet. As long as you can memorize those above equations, the nuclear balancing equations are pretty easy to solve. These are a few other notes on beta decay. I'm going to have you copy them down, but I'm not going to read them out loud. I just want to point out the bottom one that says if there isn't a positive or negative charge given for beta, assume it's beta negative, which means it's an electron. So sometimes problems will just say a beta particle instead of a beta minus particle, and when they do that, assume that they mean a beta minus particle, which is an electron. Gamma radiation and decay is the easiest one of the three to understand. A gamma ray is a photon with a very short wavelength and high frequency. It's actually the highest energy part of the electromagnetic spectrum. The symbol is a Greek letter gamma, which looks kind of like a Y, and it has no charge because it's just a photon. It has the lowest ionizing power of the three types of radiation, but it has the most penetrating power. It can be stopped by lead, but it takes much more to stop it than the other two particles we talked about. So gamma decay happens after alpha or beta decay. An electron is excited and releases a large amount of energy as it drops energy levels. So remember I talked about in a previous video, which I've linked in the description, that as electrons drop energy levels, they emit photons. After a nucleus has experienced radiation, its electrons drop in energy levels and release gamma photons. You can see, according to the gamma equation on the top, that the nucleus itself is not changed at all by gamma decay. It just emits a gamma particle with no proton or neutron number. As an example problem, a uranium atom emits a gamma particle. Write the nuclear equation to represent this. This is the easiest of the three because the uranium atom is just not affected by losing that photon. Some of its electrons are in a lower energy state, but that's just not really accounted for in nuclear equations. These are some general things you'll have to remember. If you're trying to figure out which type of radiation occurred, if the atomic mass changed, alpha decay occurred, and if the proton number changed by an odd number, beta decay occurred. Just one last thing that you may have noticed, but I want to make clear. You can see that the alpha particle has much more mass than the beta particle, and the beta particle has more mass than the gamma particle. One last observation about these particles I want to make is how they move in magnetic fields.
This is a throwback to the corner right-hand rule, which we used earlier in this course. If you don't know what that is, I've left a link to my lecture on that in the description. So these particles also have charges, so we can actually use the right-hand rule to understand how they'll move in a magnetic field. If I use the right-hand rule on this alpha particle because I know it's positively charged and the field is pointing out of the page, I find that the force is pointing to the right. On the beta minus particle, I find it's pointing to the left. On the beta plus particle, it's pointing to the right. And because the gamma particle has no charge, there's no force on it either. One other thing you'll notice is that because the alpha particle has twice the charge of either beta particle, it has twice the force as well. So if these particles were to move in a magnetic field, this is what each of their motions would look like. The alpha particle noticeably has much more mass than other types of radiation, so it moves in a much larger circle than the others in a magnetic field. A beta minus particle, in comparison, will move in a tighter circle. This is actually an exaggeration. It would actually be a much, much smaller circle than the alpha particle because the mass is so different. The beta plus particle would move in the same way as the beta minus particle, but in the opposite direction. And the gamma particle wouldn't be affected by the magnetic field at all because it doesn't have a charge, so it would just move straight. So there are times when you'll be asked how each of these charges would move in a magnetic field. So to understand that, you'll have to know their charge, the right-hand rule, and how their different masses compare to each other. So that's everything you need to know about alpha, beta, and gamma radiation. This lecture is about half-life. Before we talk about half-life, I want to remind you that when we're talking about nuclear radiation is random, which means it can't be predicted which nucleus in a radioactive substance will decay. Even if we were able to rewind the entire universe and observe it again, it's possible that a different atom in the material would decay. And it's also spontaneous, which means it cannot be predicted when a nucleus will decay. It could be very shortly after we start the time, but if we rewind the universe and observe the exact same thing again, the exact same process could take a much longer time. This is an issue for us because we need some way of predicting how radioactive substances will behave, but they're fundamentally random. To understand random processes like radioactive material, we use an idea called the law of large numbers, which says if you repeat a trial a very large number of times, the fraction of each possible result will be close to the probability of that result for each individual trial. I'll give you two examples of what I mean. Let's say that we have a coin where one side is red and the other side is blue. This means that the probability of flipping the coin and have the red side land facing up is 50%. This makes it impossible for us to predict if we flip the coin which side will come up next. Right now I have no idea what the next side will be. Here I could say, oh, I've had two reds in a row, so maybe the odds are higher that the next one will be blue, but that's not actually true. Every single time we flip it, it's 50-50, so we're just as likely to get red on the next time as any previous times. So it's totally random, and on an individual level, we can't predict what the coin will be for any one trial. And this is kind of like our situation with individual radioactive atoms. However, if we flip the coin a very, very, very large number of times, the odds are extremely high that if we then found the percentage of how many times it came up red and how many times it came up blue, would be about 50% for each. About 50% of the flips would be red and about 50% of the flips would be blue. The odds of that happening for very large numbers are very high, and they become even larger the more times we flip it. So this is what the law of large numbers is telling us. It's telling us that the fraction of each possible result, the fraction of red results and blue results, will be very close to the probability of those results. So the probability of red is 50%, and if you flip the coin, say, 1,000,000 times, the odds are very good that about 50% of those flips will be red, and about 50% will be blue. This is a way that we can still make predictions about fundamentally random events. Similarly, the odds of rolling any one number on a die are exactly 1 in 6. And so what this means is that if you took a single die and rolled it 1,000,000 times and then organized the results, you would find that each individual result occurred about 1/6 of the time. You would get the die landing on 1 about 1/6 of those total 1,000,000 rolls. So again, you can see that the fraction of the results with that number is equal to the fraction of the probability of that number if we repeat an event a very large number of times. So luckily for humans, there are a very large number of atoms in a sample of a radioactive substance. So even though we can't predict when an individual atom will decay, we can still use the law of large numbers to predict how long it will take for large amounts of atoms to decay. And this is where we get to the idea of half-life. Half-life is the amount of time it takes for exactly 1/2 of a radioactive sample to decay. Samples of the same isotope always have the same half-life, regardless of how much of the sample is physically present. We use the variable lowercase t with a subscript of 1/2 to symbolize half-life, and we can use any unit of time to measure it.
This is a visualization of what half-life means. Mercury-210 has a half-life of 10 minutes and it decays into thallium-210. So I'm going to symbolize mercury with green and thallium in blue. This rectangle will symbolize how much mercury and thallium I have. It's all green right now, so that means it's all mercury and hasn't decayed to thallium yet. And I'll imagine that this is 64 kilograms of mercury. So we're starting with 64 kilograms. There's no thallium present yet and no time has passed. If mercury-210 has a half-life of 10 minutes, that means that after 10 minutes pass, half of the mercury will have decayed into thallium. So at the 10-minute mark, I only have 32 kilograms of mercury left. 32 kilograms are now thallium, 10 minutes have passed, and 1 half-life has passed. So the half-life is always how long it takes for half of the sample to decay. So if I allow another 10 minutes to pass, half of the remaining sample is going to decay. So now after 20 minutes, I only have 16 kilograms because that's half of 32, which means 48 kilograms are now thallium. So 2 half-lives have passed. This is using the law of large numbers because mercury having a half-life of 10 minutes means that the probability of any one atom of mercury decaying into thallium in 10 minutes is 1/2. So for any individual atom, we can't meaningfully predict whether it will decay or not, but for very large numbers of atoms, we know that 1/2 of the atoms that we have will decay. And we can keep going and letting time pass. After another 10 minutes, another half of the sample will decay, so we're now left with 8 kilograms. And if we do that again, we're now left with 4 and 60 kilograms of thallium. And we could just go on like this indefinitely and continue to allow more half-lives to pass. Before we go on, I just want to alert you to a common mistake students make when they're first learning this. Some students will look at this situation and say, okay, if we have 64 kilograms of mercury and the half-life is 10 minutes, after 10 minutes pass, half of it will decay, and after the next 10 minutes, the other half will decay, and so now there's none left. But this is incorrect. This is not what happens. It's always 50% of whatever's left over. It's always half of whatever's left over after those 10 minutes. So it keeps dividing in half and dividing in half and dividing in half over and over again. So it's not the case that the material completely disappears after 2 half-lives. Another thing you'll notice is that it doesn't matter how much mass we start with. If the substance has a half-life of 10 minutes, after 10 minutes pass, it's always going to have half of whatever that starting substance was. So here I started from 2 kilograms, and you can see these values are very different from my other equation, and you can see these masses are very different from when I started with 64, but the same thing is happening. After every 10 minutes, we have half of the mercury that we had before, and the rest has become thallium. This equation is actually not given in your IB Physics data booklet, so I'm not going to talk about it too much, but this is the general equation that describes half-life. The final amount of a substance is equal to the original amount multiplied by 1/2, raised to the power of the time passed over the half-life of the object. That exponent is equal to the number of half-lives that have passed. So if I use the numbers that I had in my first example, you can see that each one individually fits this equation. So this is an intuition for why that equation works. But you're not expected to memorize that. You're just expected to memorize the basic definition of half-life. So again, this equation is not actually given in the IB Physics data booklet, and we'll use a simpler method for solving half-life problems. Just a few more notes. Most half-life questions ask about how much activity of the sample remains after a certain amount of time has passed. This is another way of saying the radioactive isotope, since the isotope is decaying to a different isotope that is less radioactive or less active. The unit of radioactivity is 1 becquerel, or 1 radioactive decay per second. We write the unit as BQ in problems. The fact that radioactive substances have half-lives causes specific patterns to show up on mass time graphs, where we graph the mass of a radioactive isotope on the y-axis and the time that has passed on the x-axis. So as an example, when no half-lives have passed, the original mass of the object is present. After 1 half-life has passed, exactly half of the mass remains. And after another half-life, half of that mass is present. And so we keep going up 1 half-life at a time on the x-axis and cutting the y-axis value in half to fill out the rest of the graph. And if I draw a line through it, this is what it looks like for the original isotope. And because the daughter isotope, the thing that the original isotope is decaying into, gets its mass from the original, the daughter isotope graph is going to look like this. So the sum of the original plus the daughter isotope should be close to the original mass. So this pattern basically always appears for radioactive substances if you graph their mass or activity on the y-axis and time on the x-axis.
I'll finish with a few word problems and a graph problem. A radioisotope has an activity of 400 BQ and a half-life of 8 days. What is the activity of the sample after 32 days? I don't need to use that complicated equation that I talked about earlier. I can just say we start with 400, and after one half-life passed, we're at 200, and then after another half-life, we're at 100, and after another, we're at 50, and after another, we're at 25. So I can see at this point, 32 days in total have passed, so that means that my answer is 25 BQ. 4 half-lives have passed. In example problem 2, a freshly prepared sample contains 4 grams of iodine-131. After 24 days, 0.5 grams of iodine-131 remain. What is the best estimate for the half-life of iodine-131? So if we start with this sample, after one half-life of the sample passes, it's going to be at 2 grams, and after another half-life passes, it will be at 1 gram, and finally it'll be at 0.5 grams after 3. So I know 24 days is equal to 3 half-lives of this material, so one half-life must be equal to 8 days. So that would be my answer to the problem. Example 3 is a little more complicated. 2 pure samples of radioactive nuclides X and Y have the same initial number of atoms. The half-life of X is capital T subscript 1/2. After a time equal to 4 half-lives of X, the ratio of the number of atoms of X over the number of atoms of Y is 1/8. What is the half-life of Y? For any complicated physics problem, I don't want to overthink it. I just want to write down everything that I know. I'm going to call capital N subscript O the initial amount of atoms of each substance. So I know that the initial amount of X is equal to the initial amount of Y. And I know that 4 half-lives have passed for X. So the final amount of X, which I'll call N subscript F, is equal to the original amount times 4 half-lives. So that's 1/2 times 1/2 times 1/2 times 1/2, which is equal to 1/16. And I know that the original amount of X is also the original amount of Y. So I can set that equal to 1/16 times the original amount of Y. I know that the final amount of X over the final amount of Y is 1/8. Rearranging that equation, I find that the final amount of Y is 8 times that of X. And I know that the final amount of X is equal to 1/16 times the original of Y. And I find that the final amount of Y is 1/2 of the original amount of Y. So that means that exactly 1/2 of the original has decayed, which means 1 half-life of Y has passed in this time. And I know that this time is equal to 4 half-lives of X. So that means the half-life of Y is 4 times the half-life of X. So that's my answer. The half-life of Y is 4 times capital T subscript 1/2. We can end with a graph problem. This graph shows the activity of iodine-124. What is the half-life of iodine-124? And calculate the activity of the sample at 20 days. So I can start at the top here, and here the activity is 16. So if I can see how much time it takes to get to exactly half of that activity, I'll know the half-life. And I can see that the time that it takes to get to 8 is 4 days. So that means that the half-life of this substance is 4 days. And if I want to be sure of that, I can just go ahead and say, well, half of 8 is 4, so it should take another 4 days to get from 8 to 4. And that's exactly what happens. And if I do that again, from 4 to 2, another 4 days pass, and so on and so on. So that's how you find the half-life from a graph. So to find the activity at 20 days, I just take 16 and 4 days pass to 8. And after one half-life, it's at 8, so 4 days have passed. And then 8 days, 12, 16, 20. So I can see that the final activity will be 0.5, and the unit on the y-axis of the graph is multiplied by 10 to the 7th BQ. So my final answer is 0.5 times 10 to the 7th BQ, or 5 times 10 to the 6th BQ if I want to write that in correct scientific notation. That's everything that you need to know about radioactive half-life. This lecture is about mass defect and binding energy. Before we talk about these concepts, I need to introduce the Unified Atomic Mass Unit. We just write that as lowercase u. This is a unit used for measuring very small mass. We use it to measure the mass of nuclei, protons, and neutrons. So 1 U is equal to 1.661 times 10 to the negative 27th kilograms. The reason we use this is that when we're working with very small objects like protons and neutrons, it would be kind of a pain to write out tens with these very low exponents for every single mass that we record. So instead we just record them in unified atomic mass units. This is the mass of a proton and a neutron in an atomic mass unit. And this is what they would be in kilograms, but I'm going to focus on atomic mass units for now. To introduce mass defect, I'm going to start with this question. Based on these masses of protons and neutrons, what would we expect the mass of a carbon-12 atom to be? And for now, I'm going to ignore the mass of electrons just because they're so small. So I know that a carbon-12 atom has 6 protons, based on the symbol that I'm looking at, and the number of neutrons is equal to the nucleons minus the protons, so there are also 6 neutrons. So this is something like what the carbon-12 nucleus would look like. If I know there are 6 protons and 6 neutrons in the nucleus, I could just multiply 6 by the mass of a proton and 6 by the mass of the neutron to find the expected mass of the nucleus. So when I do that, I find that the nucleus I would expect to have a mass of 12.095646 U. And that makes sense, right? I've got 6 protons, so I multiply the mass of a proton by 6. I've got 6 neutrons, so I multiply the mass of a neutron by 6. And then I add those two things together to get the expected mass of the nucleus. The strange thing, and the theme of this lecture, is that that expected mass is actually not the mass of the nucleus. For carbon-12, the actual mass of the nucleus is actually just 12.000000 U. So I can see some mass is missing. I have less mass in the nucleus than the mass of the individual protons and neutrons that make it up, and that's strange. I find that the missing mass is equal to 0.095646 U, and this is what I would call the mass defect of the nucleus. So the mass defect of a nucleus is the difference between the expected mass of the nucleus based on the number of protons and neutrons and the actual mass of the nucleus. To find the mass defect, you're just going to take those 3 steps that I've listed on the left. It's just like what I did in that first example. I can run through 4 more examples where I find the mass defect of each, using their number of protons and nucleons and the actual mass of the nucleus. So this would be step 1, finding the number of protons and neutrons. This would be step 2, finding the expected mass of the nucleus. And then step 3 is subtracting the actual mass from the expected mass. And so each final number there is the mass defect of that atom. Before we go on, I just need to say that the unified atomic mass unit was actually based on the exact mass of a carbon-12 atom. Scientists knew there were 12 nucleons in the atom, so they divided the mass of the atom by 12 to get 1.661 times 10 to the negative 27th kilograms, which they set equal to 1 unified atomic mass unit. So this is why a carbon-12 atom is exactly 12 U. You may have noticed it was strange that that was equal to exactly 12.0000000 U. So this is the reason why. It's because U was defined as being exactly 1/12 of a carbon-12 atom. Before we talk about binding energy, I need to talk about E equals mc squared, which is easily the most famous physics equation in existence. But at the same time, many people don't actually understand what it means. This is how it appears in the IB Physics data booklet. This just means a change in energy is equal to a change in an object's mass multiplied by c squared. What this equation means is that mass can actually be changed into energy and vice versa. You can actually destroy mass by turning it into energy. And the amount of energy we can transform mass into is equal to the mass multiplied by the speed of light squared. Remember that lowercase c is a symbol for the speed of light? If this sounds strange to you, it's because you probably haven't ever seen it in person. Mass changing into energy very rarely happens on Earth. It mostly happens in nuclear reactions. This equation does imply that a huge amount of energy is contained in even just a little mass. For example, the mass of a pen is 0.006 kilograms. And if we imagine that we were able to get all of the energy that exists in the mass of this pen out of the pen, if we were able to convert all of the mass of the pen into energy, to figure out exactly how much energy that would be, I can just plug this into E equals mc squared, where again, c is 3.00 times 10 to the 8th meters per second. When I multiply that out, I get about 5.4 times 10 to the 14th joules, which is a really gigantic amount of energy. That's equal to about 500 kilotons of TNT. Just to visualize this a little bit more, if you go to the website Nuke Map, you can actually enter in a nuclear explosion with the exact amount of kilotons of TNT that you would like it to be equal to. So if I drop a nuclear bomb worth 500 kilotons of TNT on my home city of Washington, D.C., I can see that it basically destroys the entire city. So that one little pen actually contains enough energy inside of its mass to destroy an entire city, which is pretty wild. And this is actually the basis of how nuclear bombs work as well. I've left a link to the Nuke Map website in a description of this video. So E equals mc squared is telling you that you can transform mass into energy, and there is a huge amount of energy contained within mass. The problem is that it's very difficult to change mass into energy. We can now talk about the binding energy of an atom. So the binding energy of a nucleus is the energy required to combine individual protons and neutrons into the nucleus. Some of the mass of protons and neutrons is lost to create the binding energy. So this is a situation where mass is changed into energy using E equals mc squared. So this is what happened to the mass defect. This is where that missing mass of an atom goes. So binding energy is always equal to mass defect times c squared. As an example, if we have 6 individual neutrons and 6 individual protons, and we want to combine them into a single carbon-12 atom, I know that before anything happens, their individual total mass is going to be the sum of all the masses of the individual protons and neutrons, so that mass is 12.095646 U.
And when you combine them into a carbon-12 nucleus, they actually sacrifice some of their mass and turn it into binding energy, energy that holds them together in the nucleus. So they're less massive than they were before, and now their total mass is equal to exactly 12U. So the mass defect here is 0.095646U. So that's exactly how much mass was changed into binding energy to hold these particles together in the nucleus so that they won't repel each other. And to figure out exactly how much energy this is, I'm going to change this mass into kilograms so I can use it in E equals mc squared. And usually we like to record binding energy in electron volts or mega electron volts because that's a more manageable number. And just a quick note, if you're confused about how I'm converting from joules to electron volts, I've left a link in the description of this video to my lecture on how to go from joules to electron volts. So converting this to an electron volt and then to a mega electron volt gets me a final answer of 89.4 mega electron volts. So these protons and neutrons started off as individual particles with a total mass, and then to combine together, they actually had to sacrifice some mass and turn that mass into energy. And they had to sacrifice exactly enough mass to create 89.4 mega electron volts of binding energy to hold them together in the nucleus. That last step where we went from a unified atomic mass unit to a kilogram to a joule to an electron volt to a mega electron volt was a lot of steps, and we actually don't need to follow every one of those steps every single time we do a problem. Because if you have a mass in unified atomic mass units, to convert it to kilograms, you multiply it by this factor label, and then you can multiply by c squared to get the energy, and then you can convert from joules to electron volts, and then from electron volts to mega electron volts, and that will be the energy contained in that mass in mega electron volts. Because you would always have to multiply by the exact same factors here, you can actually combine them all into just a single value, which is 931.5 mega electron volts per c squared over 1U, and that will also get you the energy in mega electron volts. So one unified atomic mass unit will always be equal to 931.5 mega electron volts per c squared. And that unit makes sense because we know that because energy is equal to mass times the speed of light squared, the mass will be equal to the energy divided by the speed of light squared. So it makes sense that we have a unit of energy per c squared. And this value is actually given in the IB data booklet, so you will never have to memorize this when you're doing problems. You just have to understand what it means that one unified atomic mass unit is equal to that amount. It literally means that according to E equals mc squared, if you convert one unified atomic mass into energy, you get exactly 931.5 mega electron volts. So this is all the information that's given about protons, neutrons, the atomic mass unit, and E equals mc squared in the IB physics data booklet. So you can see that the proton and neutron rest mass are actually already given as energy values, and you're also given the unified atomic mass unit in energy as well. I just need to go over 2 notes on binding energy before we go into some practice problems. So binding energy is the amount of energy that nucleons lose in order to bind together. This means binding energy is also the energy that needs to be added to nucleons to separate them into individual nucleons. So binding energy is the minimum work required to completely separate nucleons of an atom, as well as the energy that the nucleons themselves need to sacrifice in order to bind together. So when nucleons bind together, they sacrifice some mass, so they're also sacrificing some energy into binding energy. And if we want to separate those nucleons, we have to add in some energy from outside to give them back that energy that they lost to binding energy so they can exist as individual separate atoms again. So whenever a question asks how much energy is required to separate the nucleons of an atom, it means what is the binding energy of the atom. This other note that you have to remember is that the force involved in holding nucleons together is the strong nuclear force, which I discuss in a separate lecture on the 4 fundamental forces, which is linked in the description. So here you just need to know that there's a connection between binding energy and the strong nuclear force, where adding binding energy increases the strong nuclear force holding the nucleons in place. We can now move into some example problems. Example 1 says, what is the minimum work required to completely separate the nucleons of this atom? So remember, the minimum work required to separate the nucleons is just a code word for the binding energy. They mean the same thing. So I just need to find the binding energy, and to do that, I'll start by finding the mass defect, and I start that by finding the total mass that I would expect this to have. So I have 92 protons, 143 neutrons. So this is the mass I would expect the atom to have, and then I subtract the actual mass to find the mass defect, which I can see is 1.864557 U. And then I just have to convert that to energy by multiplying it by a factor label, because I know that in a unified atomic mass unit, you have exactly 931.5 mega electron volts per c squared. So when I multiply that out, this is what I get. And then just plugging that into E equals mc squared, that gets rid of the c squared, so I'm left with 1,737 mega electron volts. So that's the minimum work required to completely separate the nucleons of this atom. Example number 2 says, what is the total binding energy of this atom? So I'm going to solve this problem in a slightly different way than the first one. There's no reason why I'm doing this other than to show you a different method you can use. But because you know the energy contained in the mass of a proton and the mass of a neutron, you can use that to find the total energy in all of the mass before these protons and neutrons combine. And then I can convert the actual mass into the energy that's contained inside of it. So if I subtract the energy of the actual mass contained in the nucleus from the original energies of the original protons and neutrons, I get the change in energy of their mass, which is actually equal to the binding energy. So 485 mega electron volts would be equal to the binding energy of this atom. So that's another method you can use for finding binding energy. Example 3 says the binding energy of this nucleus is 1580.43 mega electron volts. What is the actual mass of this nucleus? So here I'm not given the actual mass, I'm given the binding energy. So I'll start by finding the expected mass. And once I do that, I can use E equals mc squared and the binding energy to find the mass. So if I convert this mass back to unified atomic mass units using a factor label, I find that it's equal to 1.696650 atomic mass units. So I know that the original mass minus the binding energy mass is going to be equal to the actual mass of the nucleus. So when I subtract that, this is what I get. So that will be the actual mass of this nucleus. In example 4, the mass defect of an atom is 2.202107 times 10 to the negative 28th kilograms. What is the binding energy in mega electron volts? So to find that energy in joules, I just multiply the mass by the speed of light squared, and this is what I get. So I just convert that to electron volts using a factor label, and then convert to mega electron volts using another factor label. So this is the answer that I get for the number of mega electron volts in that mass defect. So that's the binding energy of that atom. So that was your intro to mass defect and binding energy. This lecture is about binding energy per nucleon and stability. Binding energy per nucleon is the total binding energy of an atom divided by the number of nucleons in the atom. We care about it because useful patterns appear in the binding energy per nucleon of different atoms. The equation is very simple. To find the binding energy per nucleon, you just divide the binding energy by the number of nucleons. And if you rearrange that equation, you can see that the number of nucleons times the binding energy per nucleon is equal to the total binding energy of the atom. I explained how to find the binding energy in a previous lecture that I've linked in the description. I'll do 2 example problems where I find the binding energy per nucleon for these 2 atoms. So I can see I'm given the actual mass, and I remember from this previous video, to find the binding energy, I find the mass defect. And when I identify that mass defect, I determine how much energy is contained inside of it. These are the total binding energies of each atom. So to find the binding energy per nucleon, I literally just divide the binding energy by the number of nucleons. So I find that uranium-235 has 7.391 mega electron volts per nucleon, and iron-56 has 8.554 mega electron volts per nucleon. Binding energy per nucleon is usually measured in mega electron volts per nucleon. We say that a nucleus is more stable when it has more binding energy per nucleon. This is because more energy is required to remove any single nucleon from the nucleus. So as an example, if we compare uranium-235 and iron-56, uranium-235 is going to have more binding energy than iron. But if we compare the binding energy per nucleon, we can see based on the answers I got on the bottom right, that iron actually has more binding energy per nucleon than uranium. So even though uranium has more binding energy in total, iron has more binding energy per nucleon. Each individual nucleon gets a larger share of the binding energy, and so we would actually say that iron is more stable than uranium, even though uranium has more binding energy. Because stability does not just depend on the total binding energy, it depends on what share of that binding energy each individual nucleon has. Each individual nucleon of iron requires more energy to remove it from the nucleus, so therefore iron is more stable than uranium. It's less likely for nucleons to be removed. Graphs of binding energy per nucleon versus number of nucleons are a very common tool that we use in nuclear physics to understand a few important patterns about stability and nuclear fission and fusion. The graph shows the binding energy per nucleon of an atom on the y-axis and the number of nucleons in the atom on the x-axis. I have 4 elements here: helium, lithium, beryllium, and boron, with 4, 6, 8, and 10 nucleons respectively. And if I went through the same process of finding the binding energy per nucleon as I did in the beginning of this video, these are the binding energies that I would find for each specific element. If I were to place these on the graph, it would look something like this. Helium would go here because it has 4 nucleons and 7.1 mega electron volts per nucleon. And then lithium would go here, beryllium would go here, and boron would go here.
And these values are fixed. All atoms of the same element and isotope will have about the same binding energy per nucleon. So this graph is telling me where all atoms of that element and isotope appear on the binding energy per nucleon per number of nucleons graph. If I expand this graph to include all elements, this is the general shape that appears. Understanding this shape is going to be really important going forward. One important thing I want you to notice is that the binding energy per nucleon generally increases as you go up the number of nucleons until you get to iron 56, Fe56 specifically. Iron has the very most binding energy per nucleon of any element, so we say it is the most stable element. Remember, the more binding energy per nucleon an element has, the more stable it is. And I can see that after iron, the binding energy per nucleon begins to drop off, and elements actually get more and more unstable. I can see that uranium-235 and 238 at the very end are actually relatively unstable compared to iron. IB questions about this graph usually simplify it into a shape like this. So instead of that complex jagged structure, it's just a simple curve that looks like this. So this is how it usually appears in IB tests and textbooks. There are going to be some important facts that you'll need to know about this graph. First of all, the higher on the y-axis an element is, the more binding energy it has, so the more stable it is. And the most stable element is iron 56, so it's at the very, very top of the graph. The x-axis measures the number of nucleons in the element, and the y-axis measures the binding energy per nucleon. There are additional facts about fission and fusion, but this lecture doesn't cover those specifically. That's going to be in the next lecture, which I've linked in the description. One last thing to note about binding energy per nucleon is that a common IB question has this form. If this is the average binding energy per nucleon of element X, what is the total energy required to completely separate all the element's nucleons? Remember from the binding energy lecture that the total energy required to completely separate all nucleons in an atom is the binding energy of the atom. So to solve these problems, you're just going to multiply the binding energy per nucleon by the number of nucleons to get the total binding energy. So as an example, the average binding energy per nucleon of the oxygen-15 nucleus is 7.5 megaelectron volts. What is the total energy required to separate the nucleons of one nucleus of oxygen-15? So we know this is the binding energy per nucleon, so I would just multiply that by the number of nucleons. Because this is telling me that the average nucleon has 7.5 megaelectron volts, so the total energy will just be 7.5 megaelectron volts times 15. So that gets me 113 megaelectron volts, so that would be the total energy required to separate the nucleons of one nucleus of oxygen-15. So that's the basics of what you need to know about binding energy per nucleon and stability. In the next lecture, we're going to talk about how this is connected to fission and fusion. This lecture is about nuclear fusion and fission and energy in nuclear equations. To start off, we can just define the two terms. Fusion is the joining of small particles together to give larger ones, and fission is the splitting of large nuclei into smaller ones. I have an example for each below. You can see in the fusion example, two smaller nuclei are combining into a single larger one. And in the fission example, a single large nucleus is being hit with a single neutron, which causes it to split into two smaller nuclei plus a few extra neutrons. You'll notice that in both examples, the nucleon and proton numbers are conserved across the decay. At the beginning and end of both equations, there are the same number of nucleons and the same number of protons. We remember from the last few lectures that to bond together, nucleons release energy. Binding energy is the energy individual nucleons have released in order to bond. This means that the more binding energy per nucleon an element has, the more energy each individual nucleon has released. So as we go up this graph, this tells us that more energy has been released by each individual nucleon. We can use a binding energy per nucleon versus nucleon number graph to understand something important about fusion and fission. Let's say that I have a particle of neon. I can see that that has 20 nucleons, so that's going to appear here on the graph, and the graph is telling me that neon has about 8 mega electron volts per nucleon. And let's say that I want to combine two neon atoms together into a single calcium atom. So this would be an example of nuclear fusion, where we're combining two elements together into a single larger element. Students looking at that fusion reaction might mistakenly assume that when these two elements bind together in fusion, they're just sharing their total binding energy and their total number of nucleons. And so no additional binding energy is added to this system. But that's not actually what's going to happen here, because I can see using this graph that the element with 40 nucleons is going to have more than 8 mega electron volts of energy per nucleon. So that means that when fusion occurs here, these two particles will not only bind together, but each individual nucleon will also release some additional binding energy.
So if we start on the graph where the 20 nucleon number is and rise up to where the 40 nucleon number is on the energy value, I can see that as a result, each individual nucleon had to sacrifice some additional mass to gain some additional binding energy per nucleon. So what I'm trying to get across here is that when fusion or fission occur, the nucleons don't just share their binding energy with each other, because if they did that, the binding energy per nucleon wouldn't change. What also happens is that the mass of each individual nucleon drops to release some additional binding energy. So based on the definition of fusion and fission, fusion would involve the movement to the right on this graph because it involves going from a smaller nucleon number to a larger nucleon number. And fission would be going from right to left because that involves going from a larger to a smaller nucleon number. I know that iron, Fe56, is the most stable element. Before that, the binding energy per nucleon goes up, and after the binding energy per nucleon goes down. So I can see that on this side of the graph, if fusion occurs, if you move to the right on the graph, the binding energy per nucleon goes up. So that means that fusion releases energy, because binding energy is released energy from the mass of nucleons. So in the area to the left of iron, if fusion occurs, fusion is going to involve the release of binding energy. And looking to the right of iron, I can see that fission is going to release energy, because here, if I move to the left on the graph, which is what fission does, the binding energy per nucleon also goes up. So that means that each nucleon has to release some energy. What I'm trying to get across here is that to the left of iron on this graph, fusion is what's going to release binding energy. And to the right of iron on this graph, fission is what's going to release binding energy. Nucleons can naturally sacrifice mass to emit binding energy, but in order to gain mass, they need an external source of energy. This means that an atom can only change its nucleon number spontaneously when its binding energy per nucleon goes up. So what this tells us is that fusion and fission can only really happen spontaneously in atoms when they're gaining binding energy per nucleon. So that means that fusion occurs naturally to the left of iron and fission occurs naturally to the right of iron. But if we were to swap these positions, these reactions involve a drop in the binding energy per nucleon, so they require an external source of energy in order to occur. Those are the main facts about fusion and fission that you'll need to know. The last little piece of information is, where does released binding energy actually go when fusion and fission occur? When nuclear fission or fusion causes binding energy to be released, the energy is emitted as kinetic energy in the particles after the reaction. Particles always obey the conservation of momentum after they gain the kinetic energy from the reaction. So I'm going to talk about this more in a moment. I'm just going to do some example problems first involving fission, fusion, and binding energy. The first example problem we'll do is identifying fission and fusion. This is just asking you to identify the following reactions as either nuclear fission or fusion. I can see in the first example, two smaller particles are combining to make a single larger particle, and they emit a neutron as well. But the main thing to notice here is that a particle with more protons and nucleons exists after this reaction than did before. So this means that this is an example of smaller nuclei going to a larger nucleus. So that means that this is an example of fusion. Whereas in the bottom example, I can see I have a single very large nucleus of uranium breaking into two smaller atoms and 3 neutrons. So because this is a larger nucleus breaking up into smaller nuclei, this is an example of nuclear fission. So that's how you would identify which is which. We're now ready to talk about energy released in nuclear equations. Deuterium undergoes fusion according to this following reaction, and the following data are available for binding energies per nucleon in each individual particle. This is asking you to determine in mega electron volts the energy released by this reaction. So you'll remember that the energy released is going to be the change in binding energy before and after the nuclear fusion or fission event. In this case, this is fusion. So to understand the energy released, I just need to know the total binding energy before and after the reaction. So before, I know that the binding energy per nucleon of deuterium is 1.12 mega electron volts per nucleon, and I can see that there are 2 nucleons, so that means that the total binding energy in this atom is 2.24 mega electron volts. And it's the same here. I know that the binding energy here is 2.78 mega electron volts per nucleon, and there are 3 nucleons here, so that means that this is the total binding energy of hydrogen 3, and that last hydrogen atom only has 1 nucleon. And the function of binding energy is to bind nucleons together with other nucleons. And so if you only have 1 single nucleon, you don't need any energy to bind it to others because there are no other nucleons. So that means the binding energy of that last hydrogen atom is just 0. So I can see that the total binding energy before the reaction is 4.48 mega electron volts, and after it's 8.34 mega electron volts. So that means that these particles had to release additional binding energy in order to bind together. So just subtracting before from after, I can see that the total binding energy released is going to be 3.86 mega electron volts. So that's how much energy was released in this fusion reaction. Here's another example. A stationary nucleus of uranium-238 undergoes alpha decay to form thorium-234. The following data are available for the energy released in the decay, the binding energy per nucleon for helium, and the binding energy per nucleon for thorium. And this is asking us to calculate the binding energy per nucleon for uranium-238. So I know that alpha decay means the release of a single helium atom, which is why the equation is written in this way. So we just need to understand the total binding energy that exists after this alpha decay and use that along with the energy released to find the uranium's energy. Starting with thorium, I know that the binding energy per nucleon is 7.6, so I multiply that by 234 nucleons. And for helium, I know that it's 7.07 mega electron volts, and I multiply that by 4 nucleons. So these are the numbers that I get for the binding energy of each particle. So that means that the total energy after the decay is 1,806.6 mega electron volts. That means that the energy before the decay, because energy is being released from the mass of the nucleons, there's actually going to be less energy before the decay than after the decay. So I'm subtracting the energy released. So that means that before the decay, the total binding energy that exists is 1,802.31 mega electron volts. So that's the binding energy of the uranium-238 atom. So to calculate the binding energy per nucleon, I just divide that value by 238 nucleons, and I get a final answer of 7.57 mega electron volts per nucleon. So that would be the binding energy per nucleon of the uranium-238 atom. After decay, what is the value of the ratio of the kinetic energy of the alpha particle to the kinetic energy of the thorium nucleus? This relies on some concepts that we learned in previous units. If the uranium decays into thorium and helium, I know that the energy released is going to exist as kinetic energy in the particles. So that means that these particles are moving. And I know specifically that they're going to be moving away from each other because we assume the uranium is beginning with 0 velocity, and because of the conservation of momentum, the total momentum before and after the decay must equal 0. So this means the momentum of thorium must equal the momentum of the helium, because the two are canceling each other out. So we can use this to solve the problem. We can say that the kinetic energy of the helium over the kinetic energy of the thorium is what we're looking for. And there's a special equation for kinetic energy that relates it to momentum, where kinetic energy is equal to the momentum squared over 2 times the mass. And I know that here the momentum of each individual object has the same magnitude, because they're canceling each other out to 0. So that means that the momentum on the top and bottom are the same, and the 2's are also obviously the same number, so I can cancel those out. And when I cancel everything out, I'm left with this simple equation, where the ratio of the kinetic energy of helium to thorium will actually be equal to the ratio of the mass of thorium to helium. And because the difference in mass between protons and neutrons is so small, I can just count the number of nucleons for now and say the mass of thorium is 234 nucleons, the mass of helium is 4 nucleons, so that means that the ratio is 58.5. So that's how you would solve that problem. The next type of example is using a binding energy graph to estimate energy loss. This problem is asking us to use this graph to show that the energy released when 2 hydrogen-2 nuclei fuse to make a helium-4 nuclei is approximately 4 picojoules, which is 4 times 10 to the negative 12th joules. I can use this graph to understand the binding energy per nucleon of hydrogen-2, that's here. I can see that's about 1.2 mega electron volts. And the binding energy per nucleon of helium-4 is here. So that's going to be about 7.2 mega electron volts. So I know that I'm fusing 2 of these hydrogen-2 particles to make a single helium-4 particle. So I can just find the individual binding energies of each particle using the numbers that I got from the graph, and then compare the total energy before and after. So I can see that the energy change is 24 mega electron volts. So that's the energy released. So I just need to convert that to joules. First, I'm going to go from mega electron volts to electron volts. So there's 10 to the 6th electron volts for every mega electron volt. And then I can go from electron volts to joules. And when I do that, I see that this is roughly 4 times 10 to the negative 12th joules, which is equal to 4 picojoules. So that's how you would use this graph to find the energy released.
The final question is just a comparison between mass and energy. In a fission reaction, the total mass and the total binding energy before the reaction are Mi and Ei respectively, where the binding energy is defined as a positive quantity. After this reaction, the total mass is Mf and the total binding energy is Ef. Which of the following correctly compares the total masses and the total binding energies? In a fission reaction, the total mass and the total binding energy before the reaction are Mi and Ei respectively, where the binding energy is defined as a positive quantity. After the reaction, the total mass is Mf and the total binding energy is Ef. Which of the following correctly compares the total masses and the total binding energies? So I know that for both types of reactions, binding energy is released. So there's going to be more binding energy after the reaction than before. So I already know that Ef will be greater than Ei. So now we just need to figure out what's going to happen with the mass. So this graph shows the nucleon number going down, but that's actually not really a correct way of reading it, because I'm trying to understand what's going to happen to the total mass, and nucleons are conserved. So each individual particle after the fission is going to have less nucleons, but this is asking about the total mass. And in total, there will be the same amount of nucleons present as before. They'll just be split up into multiple particles instead of existing in one single particle. So that alone doesn't tell me whether the mass is getting bigger or smaller. However, I do know that each individual nucleon had to sacrifice some mass to get that additional binding energy, because I know 100% that there is more binding energy than before. So that means that each individual nucleon must have sacrificed some mass. So because there are the same number of nucleons as before, just split up into more particles, and each individual nucleon sacrificed some mass, I know 100% that there must be less mass than before. So M final is going to be less than M initial, so the answer here is going to be D. And that's everything that you need to know about fusion, fission, and energy in nuclear equations. This lecture is about stellar parallax, which is a tool that we use to measure the distance to nearby stars. To understand what I mean by parallax, I'm going to have you do a quick demo. I'm actually going to have you hold your thumb up very close to your face like this, and close and open each of your eyes back and forth just like that. And as you do that, you can see that your thumb, the position of your thumb, moves a lot compared to whatever background you happen to be looking at. So that probably looks something like this when you hold your thumb up in front of your face like that. What I'm going to have you do next is hold your thumb very far away from your face like this and do the same thing. Just open and close each eye and observe how the position of your thumb compared to the background that you're looking at changes. When you do that, it probably looks something like this. The position of your thumb changes a little bit, but not as much as when it was very close to you. This is the parallax effect. This is what we're going to be talking about throughout the lecture. Parallax is what happens when the position of an observer changes, and as a result, the objects that the observer can see change their position in the observer's field of vision in comparison to farther away objects that don't change their position as much. We experience this effect all the time when we go outside and begin to move more quickly. Objects that are closer move more in our field of vision compared to objects that are farther away. Here, this tree is moving a lot, the mountain is actually moving a tiny little bit, and the sun is not moving at all. So just looking at this animation, your brain kind of automatically assumes that the tree is closer than the mountain, and the mountain is closer than the sun, because the tree moves more in your field of vision compared to the mountain, and the mountain moves more compared to the sun. So the movement of objects in our field of vision in comparison to very distant objects can tell us how close or far away they are. We care about this because we can also observe that same effect in nearby stars. If we wanted to compare this white star and this yellow star and understand which one was closer and which one was farther away, we could observe how they move in our field of vision as the Earth moves through space. And when we observe that here, it becomes pretty apparent that the white star is closer to us than the yellow star as the Earth makes its orbit around the sun. This is the focus of the lecture. Parallax is the visual effect where the position of an object relative to a background appears to change based on the viewer's position. And stellar parallax is the use of the mathematical patterns in parallax to find the distance to nearby stars. We can measure the difference in the apparent position of a star when Earth is on either extreme end of its orbit around the sun. So this is a tool that we use to find the distance to nearby stars. This is going to be kind of a complicated animation. I'm going to go through the exact geometry of how astronomers use parallax, so just make sure you're taking close notes and paying close attention to what's happening.
We imagine that we're observing the star in January, and we draw a line from our point of observation to the star. So that line looks something like this. We then wait 6 months and observe how the star's position in the sky changes based on how much the Earth has gone around the sun. Once it's been 6 months, which is the time it takes for Earth to get to the other extreme of its 12-month orbit, we can draw another line showing where the star is compared to our observations that looks like this. And this is what that line would look like in space. And as Earth returns to its January position, the star also returns to its same position in the sky that it was at in January. To find how far away this star is, I'm going to start by drawing an orange line straight out into very deep space. So both lines in January and July can be represented by that same orange line on Earth. Just because deep space itself, the background stars of the galaxy, are just so incredibly far away compared to the star that we're looking at. And so the difference between those lines becomes basically non-existent. It's kind of like if we were moving our position back and forth in comparison to a tree and observing the parallax of the tree and observing some mountains in the distance. It doesn't really matter that those two orange lines are drawn from different spots. They're both just staring off into the distance, and so they can be represented as the same orange line from our line of sight. I'm now going to label the angle that the star's position makes relative to this orange line. This is the January angle of sight, and this is the July angle of sight. And these aren't necessarily the same angles because the star could actually be somewhere up here, so we're not sure whether these angles are exactly the same or not, which is why I'm recording them as two separate values. I'm going to call this pink line the total angular distance that the star travels over 6 months. This total angular distance is going to be equal to the difference between the two individual angles of sight. This is a really important part of the parallax definition, so just make sure you're understanding why this is the case. As an example, if the January angle of sight were positive 20 degrees, and because the July angle of sight is in the opposite direction, we'll call that negative. So I'm just imagining that this is negative 20 degrees, and I'm just making these numbers up. The total angular distance would be the final angle minus the initial angle, which here would be negative 40 degrees. And this makes sense because I can see that from January to July, the star is changing its angle in the negative direction. So this is an important definition for parallax. The total angular distance traveled over 6 months is equal to the difference between the two angles of sight of the star. I'm now going to use a geometry trick in my animation down here to show that those two angles together and that total angular distance is equal to this angle right here in my drawing. And if I divide this in half using this line, this angle right here, half of the full angular distance, I'm going to call the parallax angle. This is going to be the main angle that we use for doing calculations with parallax, so it's important to have a clear idea of what this means. The parallax angle of a star is equal to half of the total angular distance it covers over a 6-month period. The reason why we care about the parallax angle is that this is going to help us find the exact distance to the star from the sun. The reason why it can help us with this is because we know the distance from Earth to the sun. Because we know that distance, and we can assume that this angle here is 90 degrees, if we know the parallax angle and we know the distance to the sun, we can use trig to identify the distance to the star. This is the distance from the Earth to the sun, 1.5 times 10 to the 11th meters, which we've labeled 1 astronomical unit, or 1 AU. So when you see 1 AU written out, that always means the exact distance from Earth to the sun. We gave that its own special unit because it's used so often in parallax equations. We can rewrite this as tangent of the parallax angle is equal to 1 astronomical unit over the distance to the star that we're measuring. And just to shorten that, I'll call that 1 AU over the distance d. The parallax angle is always extremely small because stars are always very far away from the sun compared to the sun's distance to Earth. For small angles measured in radians, tangent of theta is roughly equal to theta itself. So that means we can rewrite our equation as the parallax angle is equal to 1 astronomical unit over the distance to the star. Rewriting this to get the distance to the star we're measuring is 1 astronomical unit over the parallax angle. So this is how we find the distance to nearby stars based only on our observation of parallax over 6-month periods. Because the parallax angle is so extremely small, scientists came up with a special unit for distance in space based on the parallax equation. Before we use that distance unit, we're going to need another unit for incredibly small angles. So you already know the unit of 1 degree. For very, very small angles, I'm going to define an arc minute as being 1/60th of a degree and an arc second as being 1/60th of an arc minute. So I've written down what all of these are in comparison to each other and in comparison to radians. So you can see an arc second is a very, very small fraction of a circle. It's less than 1/millionth of a circle. Because parallax angles are so incredibly small, they will mostly be measured in arc seconds rather than in degrees or radians. So this is the new unit of distance. Instead of measuring this distance in space in meters, we're going to measure the distance in something called parsecs. 1 parsec is the distance from the sun to a point with a parallax angle of exactly 1 arcsecond. Anything that is exactly 1 parsec away will have a parallax angle of exactly 1 arcsecond over a 6-month period of observation. It's a unit of distance. So just plugging this into the equation, 1 parsec is equal to 1 astronomical unit, which is the distance to the sun, divided by 1 arcsecond of parallax angle. I can figure out exactly how far that is in meters by plugging arcseconds in as radians instead. And when I calculate that out, I find that 1 parsec is equal to 3.09 times 10 to the 16th meters. I can also convert this to light years. This is equal to 3.26 light years. So it's very close to light years, but it's useful when we're dealing with parallax specifically. For most parallax problems that we do, we'll measure the distance in parsecs and the angle in arcseconds. Here are just a few examples of different lengths in parsecs. The diameter of the solar system is 0.009 parsecs. The distance to the nearest star system, Alpha Centauri, is 1.34 parsecs. And the diameter of the Milky Way galaxy is 32,408 parsecs. The parallax method for measuring distance to other stars is limited because how far we can measure distances in space using stellar parallax depends on the smallest parallax angle we can observe. The smaller the angle, the farther the distance. You can see based on my drawings here that because the distance from the sun to the Earth stays the same, the farther the star we're measuring is from the sun, the smaller the parallax angle is going to be. So the distance we can measure is limited by how small we can measure that angle to be. And the smallest parallax angle we can currently observe with our instruments is 5 times 10 to the negative third arcseconds. Plugging that into our equation for distance gives 652 light years. So that's the maximum distance in space that we can measure using the parallax method on its own. Here's an example parallax problem. Star A travels an angular distance of 0.72 arcseconds in the sky from January to July. Start by drawing a diagram showing the Earth, Sun, and Star A and the parallax angle P used to measure the distance from the Sun to Star A. So if I were to draw a diagram of this, I would draw a circle representing the Sun, another circle representing the Earth's orbit around the Sun, and the Earth in January and July. The star that we're trying to measure, a line of observation drawn from January and July, and the parallax angle is going to be 1/2 of that full angle that the star makes in our field of observation. That's the type of diagram that you would be expected to know how to draw. Part B asks us to determine the parallax angle. That's easy. The parallax angle is just the total angular distance traveled divided by 2. That comes out to be 0.36 arcseconds. Part C asks to determine the distance in parsecs to star A. So just using this equation, I get the total distance to be 2.78 parsecs. And in part D, we're going to determine the distance in light years to star A. I'll convert using the factor label method, so I'm trying to get rid of parsecs and have light years in my answer. So parsecs go in the denominator, light years in the numerator. And when I cancel that out, I get 9.06 light years to star A. So that's how we can use everyday observations of the movement of stars on Earth to predict the exact distance to nearby stars. This lecture is about Hertzsprung-Russell diagrams of stars, which we usually just call HR diagrams. They're named after the astronomers who created them.
HR diagrams are graphs that show the surface temperature of stars in Kelvin on the x-axis and the luminosity of stars measured in proportions of the luminosity of the sun on the y-axis. Both axes are graphed logarithmically, which means that the numbers on the axis do not increase linearly, they increase by multiples of a number. So as an example, on the y-axis of this HR diagram, you can see that each additional notch is multiplied by 100 from the previous notch. And on the x-axis here, each additional notch is divided by 2. The reason we graph HR diagrams this way is that this specific format allows us to see clear patterns emerging in the properties of stars. And just for context, this is the luminosity of the sun. So each notch on the y-axis is 10 to a certain power times that luminosity. If I were to take a large amount of stars from space at random and fill out this chart using the properties of those stars, it would look something like this. There are a few different patterns that emerge on this graph, so I'm going to go through and talk about them. The first pattern you might notice is this long streak of stars going roughly linearly all the way down the graph. These are called main sequence stars. They're kind of the main type of star in the universe. They follow a consistent pattern where an increase in temperature also means an increase in luminosity. About 90% of stars in the universe are main sequence stars, and our sun is actually also a main sequence star. So our sun obviously has a luminosity of one sun, of one Earth sun, so that would be 10 to the power of 0 for luminosity. And that dot is roughly at the temperature of our sun as well. So that's where our sun would appear on this diagram. About 90% of all stars in the universe are main sequence stars. That's kind of why they're called the main sequence. It's the sequence of increasing luminosity versus temperature that most stars follow. In this corner over here, I can see that these stars are very luminous. They have a high luminosity number, but they're not very hot. This must mean that they're very large. The same energy distributed across more mass leads to a lower temperature. This means that the stars in the top right of the graph must be very large. We call these stars giants. They're very large, they're very luminous, but they're also relatively cool. There's a special class of extremely luminous and extremely large stars that we call supergiants. So this would be the area of the HR diagram where they appear. Stars that are not too luminous but are extremely hot must have a low amount of energy, but have that energy inside a very compact space to make the temperature high. So they're physically very small. We call these stars white dwarfs. They're very hot, they're not very luminous, and they're small stars. So in general, we say that stars on an HR diagram exist along a main sequence with 3 islands of red giants, supergiants, and white dwarfs. The color of a star is determined by its temperature. The hottest stars are blue, then white, then yellow, then red, and this is roughly where each color appears on the HR diagram. So any stars that have a temperature of roughly 10,000 to 5,000 Kelvin will appear as yellow. From about 13,000 to 10,000, they'll appear as white. And from 40,000 to 20,000, it's blue. And from less than 5,000, those stars appear as red. So if a dot falls within that color band, that star literally is that color in the sky. This picture on the right is a much more detailed, accurate, and color-coded HR diagram. And even with the extra detail, it's not too difficult to read and understand. So I can see that I have that main sequence of stars going up and to the left. I have a patch of white dwarfs on the bottom left. I have giants on the top right and supergiants on the top. And you can see that the axis on the left measures luminosity in terms of multiples of the sun's luminosity. And on the x-axis listed on top, you can see temperatures listed. The top of the graph is also organized by spectral type. This is a way of classifying stars by color and temperature. Stars of the same spectral type always exist in the same range of temperature. You should be aware of this, but you do not need to memorize it for IB physics specifically. So I've listed the different spectral types. The names of the spectral types are really just names for ranges of temperature and the color that the stars appear as. The letters are O, B, A, F, G, K, M, and you can see each one corresponds to a different color of star and a different range of temperature. So if a star is spectral type B, its temperature must be between 10,000 and 30,000 Kelvin. If it's spectral type K, it must be between 3,700 and 5,200 Kelvin. And just as a note, students can sometimes get confused looking at this graph and assume that this is a kind of map of the physical location of stars in space. Like it looks like it could be maybe like a strangely shaped cloud of stars. But this graph says nothing about the position of stars and is only a way of organizing them by temperature and luminosity. So this says nothing about where stars physically are in space. Astronomers have an equation that predicts the luminosity of a star given its surface area, temperature, and a constant. I'm just going to have you read through this equation. It's pretty straightforward. There's one new constant that we haven't worked with before, the Stefan-Boltzmann constant, which is 5.67 times 10 to the negative 8 watts per meter squared per Kelvin to the negative 4th. Because all stars are spheres, we can rewrite that surface area as the surface area of a sphere to get the bottom equation that includes the radius of the star. And because this is a logarithmic graph, when we hold the radius of the star constant, stars with the same radius appear on a line on the graph. So as an example, any star that appears exactly on this line has a radius of about 1/100th of the radius of Earth's sun. Stars that appear on this line have a radius that's equal to Earth's sun, and stars that appear on this line have a radius that's 100 times larger than Earth's sun. And you could draw these lines for any radius that you want. As an example, between 1 and 100, you could find a line for 10 times the Earth's sun, but we don't want to fill this up completely with lines because we could draw an infinite amount. So I'll just draw a few as an example. So we call these lines of constant radius. Any two stars that appear along the same line of constant radius have the same radius as each other. So you can see that as you go up and to the right on the graph, the radius of the stars that you're looking at, therefore the size of the stars that you're looking at, increases. This equation, luminosity is equal to the Boltzmann constant times the area times the temperature to the 4th, can be used to describe proportional relationships between the luminosity, size, and temperature of different stars. I'll use this to answer a few questions about the sizes of different stars on this HR diagram. This first question says, comparing stars A and C, which star is larger? So I can see A is in the top left, C is in the top right. I can compare their luminosity and see that they have the same luminosity. They're on the same point on the graph. And I can compare their temperatures and see that star A has a greater temperature than star C. If I take that equation for luminosity on the top and rearrange it to find the surface area of a star, this is the equation that I get. So because star A and star C have the same luminosity, but star A has a greater temperature than star C, the denominator of star A's area will be greater than the denominator of star C's area. Their numerators are the same, but there's a number in the denominator of A that is bigger than the denominator of C. So if you have a bigger denominator, that means that as a whole your number is smaller. So that means that the surface area of C is greater than the surface area of star A, which means that star C is larger than star A. So to get that information, I used information from the diagram and the equation L equals the Boltzmann constant times area times temperature to the 4th. So based on that pattern, following a horizontal line from left to right on an HR diagram leads to larger stars. This fits our understanding because if we look back here, we can see that as we go from left to right, we do get larger and larger stars. The red giants are to the right of supergiants, but they're also lower on the graph. If you were to just follow a perfectly horizontal line from the supergiants, you would get larger and larger stars in that direction. So if you draw any horizontal line between two stars on this graph, and two stars are on the same horizontal level, the star on the right will always be bigger than the star on the left. This also fits our understanding based on those lines of constant radius. I can see that as I go from left to right, the radius is increasing. We can now try comparing stars A and B and see which star is bigger here. So star A and B, star A has the greater luminosity, and both stars have the same surface temperature. Plugging that into the equation for area, if the denominators are the same, but the numerator of A is bigger than the numerator of B, that means that the surface area of A will be bigger than the surface area of B. So star A is the bigger star. Based on that pattern, we can see that following a vertical line from down to up on an HR diagram leads to larger stars. This fits our understanding. I can see that as we go up the diagram here, we go from smaller stars to larger stars. And that also fits the pattern on the lines of constant radius. As I go straight up, I can see that the radius of the stars I'm looking at gets bigger and bigger and bigger. We can now try comparing stars A and E and decide which star is bigger between the two of them here. So I can see that star A has a greater luminosity than star E, and the temperature of star A is also greater than star E. So for the area, the numerator of star A is greater than star E, but the denominator is also greater than star E. And so unless I have very specific numbers for both stars, I actually can't compare the areas of these two stars. This is not enough information on its own to be able to tell which star is bigger. So we'd need the exact numbers to know for sure which star is bigger than the other star. This also makes sense because if we think about going diagonally down the graph, I have no way of being sure exactly where that line of constant radius is unless I have specific numbers. So I don't know if by going diagonally down, I've gone below the radius where I was on before or above the radius where I was on before. Both of those lines point down. And so unless I have exact numbers, I can't just say that going diagonally and down means one thing or the other. So that's how to read HR diagrams and use the luminosity equation to predict which stars will be physically larger than other stars. This lecture is about Cepheid variables and how they're used to find distances in space. A Cepheid variable is a type of extremely luminous star that undergoes periodic changes in luminosity. So its luminosity varies, so it's a variable star. They're so luminous that we're able to observe individual Cepheid variables in other galaxies. The properties of Cepheid variables can be used to determine distances in space. Cepheid variables vary their luminosity periodically, which means they repeat over equal amounts of time. The graph of a Cepheid variable's luminosity is not a sine graph, however. The time it takes to regain luminosity is less than the time it takes to lose luminosity. We can use luminosity time graphs like the one below to identify the period of a Cepheid variable. So here I can see the period, the time it takes the Cepheid to repeat one full cycle of becoming brighter and dimmer, is 5 days. So the period of a Cepheid variable can be found on a luminosity time graph by just looking at the time between 2 points of equal luminosity. Cepheid variables have an outer layer that expands and contracts. When the outer layer is larger and less dense, more light from the core of the star can pass through and the star is brighter. When the outer layer is smaller and more dense, less light from the core can get through and the star is dimmer. So more luminosity means the star is in its larger phase, and less luminosity means it's in its smaller phase. So a very common Cepheid question is to be given a graph like this luminosity time graph and to be asked where is the star largest and where is it smallest. So it's going to be largest at its highest luminosity and smallest at its lowest luminosity. Variable stars are called Cepheid variables because the first variable star to be observed was Delta Cepheid in 1784 by John Goodricke. The reason why we care about Cepheid variables so much is that they're what allowed humans to find the exact distance to objects in space that were too far away to apply the parallax method. So a big part of this lecture is going to be about the history of astronomy and just how important Cepheid variables were to that history. Before 1908, our only method for measuring distant objects in space was parallax, and parallax only works for angles we can clearly measure. When the angles become too small, our atmosphere begins to interfere with the measurements, and so the farthest we could measure with parallax was about 30 parsecs, or about 100 light years. So we could not measure the distance to any object beyond that length of 100 light years in space. And that's an incredibly small distance to be able to measure in space compared to just how much we can observe. Just as an example, the radius of the Milky Way, if I were to draw the Milky Way as a circle, that radius is 50,000 light years. And so if we could only observe 100 light years out, this blue circle represents how far we could measure in any direction before Cepheids and before 1908. And this circle is not drawn to scale. If I were to compare this blue circle to the galaxy circle on the left, this tiny little dot at the very end of that arrow is the total range of distance we could measure before 1908 and before Cepheid variables. So you can see that's incredibly small compared to even just the Milky Way galaxy, which is just one small part of the observable universe. Cepheid variables allowed us to jump from a limit of 100 light years to a limit of 20 million light years after their discovery. So just to compare how far we could measure after we discovered Cepheid variables, if I were to place this red circle to scale inside of the purple circle, it would appear as this dot at the very end of this arrow. So Cepheid variables alone completely changed our understanding of the universe and how far away different objects were, which also allowed us to understand the shape of our galaxy and the shape of other galaxies, and eventually proved that the universe was expanding. And this gigantic step was made possible by a pattern that was observed by an astronomer in 1908. Astronomers had been aware of variable stars since the late 18th century, but in 1908, the astronomer Henrietta Leavitt observed a relationship between the period and maximum luminosity of variable stars that would allow scientists to find the exact distance of any variable star she could observe, even stars that were in other galaxies. Before we talk about how she did this, we need to observe a problem with measuring distances in space. When we were working with the brightness equation, which relates the brightness that we observe on Earth, the luminosity of a star, and the distance from Earth to the star, you may have wondered why we can't just use this equation to understand exactly how far away any star is based on its brightness. And the answer is that we don't know how luminous the star is. As an example, in the picture on the bottom left, we could imagine that star A appears brighter than star B in the night sky. we could conclude from that, oh, maybe star A is closer to us than star B, and that's why it appears brighter. But that wouldn't make sense, because it could just as easily be the case that star A is just more luminous than star B, it gives off more energy per second than star B, and star A could be farther away and still appear brighter in the sky. So what I'm trying to say is that a star's brightness alone cannot tell us how far away it is. So the brightness equation seems like it could be a useful equation for finding the distances to stars, but we would need to know their exact luminosity, how much power they're giving off, in order to use the equation to calculate that actual distance. And before 1908, scientists did not know the luminosity of stars farther away than 100 light years. Because we can always observe the brightness on Earth, lowercase b in this equation just represents the observed brightness on Earth. If we have the luminosity of a star we can observe, we can always calculate its distance, and if we have the distance to a star, we can always calculate its luminosity. But we need one in order to calculate the other, and before Cepheid variables came along, we had no way of understanding the luminosity of stars farther away than 100 light years, so we couldn't use this equation to calculate distance. Henrietta Leavitt was a computer, which at the time just meant a data analyst at Harvard, who made observations of more than 2,500 variable stars. And just as a heads up, when I say that she made observations, I mean that she observed the data recorded by other scientists, because even though she was the one to make this groundbreaking discovery, she did it without ever using a telescope herself because women were not allowed to use the Harvard telescopes in the early 1900s. Leavitt knew that every variable star had an exact period where its luminosity would get larger and smaller and repeat, and she wanted to know if there was a relationship between the period of the star and the maximum luminosity that it reached. She didn't know how luminous variable stars were compared to each other. She had the same problem that we just had looking at that brightness equation, where we can't understand the true luminosity of stars if we don't know the distance to the star. She couldn't compare how luminous Cepheid variables were compared to each other because she could only observe their brightness, and a brighter star could just be closer rather than having more luminosity. There were variable stars within the distance that could be measured by parallax, so she could find the distance of those stars and calculate their luminosity using the brightness equation, but there were not enough variable stars within that distance to get a clear pattern for what she was looking for. She came up with a really cool solution to this problem, which was to observe many different variable stars in a faraway cluster of stars, the Magellanic Clouds. She reasoned that because these stars seemed to exist in a cluster separate from other stars, they were probably all roughly the same distance from Earth as each other. We now know that the Magellanic Clouds are actually two dwarf galaxies that orbit the Milky Way. If the stars that she observed were all roughly the same distance as each other, then if star A were brighter than star B, it meant that star A was definitely more luminous than star B. So this gave her a way of understanding which star was more luminous than another star. You can see based on the picture that I've drawn, that if we're observing two different stars from Earth, and we have a good reason to think that they're the same distance away, if one star appears brighter in the sky than the other, that has to mean that that star is more luminous than the other star, because we know distance can't be affecting the brightness because the distance for both is the same. She didn't know the actual luminosity of the stars she was observing, but she could still compare their relative luminosity to their periods. So what that would mean is she could observe the periods of different Cepheid variables, just how much time it takes for them to flash from brighter to dimmer and back, and recording their relative luminosity would mean to say something like, okay, this star appears to be twice as luminous as this other star is 10 times as luminous as this other star, so even though I don't have an exact number value for that luminosity, I can still compare how luminous they are in comparison to each other, relative to each other. After observing many stars in the cluster, she found a relationship between the period of the variable star and its luminosity. If she graphed both values logarithmically, a linear graph resulted with a clear, predictable line. So this graph on the right is the actual graph that she published in her paper on Cepheid variables. The y-axis is a measurement of negative powers of 10 of the brightness observed on Earth, and the x-axis is the logarithm of the period in days of the star. And these two lines are the maximum brightness and the minimum brightness of the Cepheid variables. Because remember, they oscillate back and forth between being bright and being dim. This graph is a little difficult to read for students, so I'm going to change it into a more understandable graph here. Because she was graphing their relative luminosity compared to each other, we can say that the y-axis is made up of numbers all multiplied by some constant that we don't know. This allows us to show a proportion without knowing the actual values. This graph is similar to what her graph showed. What this graph is telling us is that if the period of one variable star is 10 days and the period of another variable star is only 1 day, the luminosity of the 10-day period star will be about 10 times as big as the 1-day period star. So even though she didn't know the true number values of the luminosity, she could get this relative comparison of the luminosities of different stars. She then argued that finding a single variable star's luminosity would change this graph from a graph of relative luminosity to absolute luminosity. Just as an example, let's imagine that somehow we found the absolute luminosity, the real true luminosity, of a variable star with a period of 1 day, and we found that luminosity to be 5 watts. That would fill in the information about what that constant is, and without making any more observations, we could take that same constant and plug it into the other values, because we know how much these stars compare to each other relatively. So we could say, I know 100% based on her observations that if you multiply the period by 10, the luminosity will also be multiplied by 10. So if I know the luminosity of a star with a period of 1 day is 5, I definitely know that the luminosity of a star with a 10-day period is definitely 100% 50. So if you have an absolute luminosity graph, you can find the luminosity of a star just using its period and not using its distance. So just to review what I've said so far, Leavitt observes variable stars in the same cluster, which all have the same distance to Earth, which allows her to observe how luminous the stars are relative to each other, but not their absolute number value, which allows her to make this graph and find this pattern in the luminosity versus the period of the stars, which would tell her the true luminosity of any variable star if she can find the luminosity of just one single variable star, because if she found that, she could fill in all the missing information in the chart, and that would allow her to find the absolute luminosity of any variable star just given its period, which is easy to observe from Earth. So if she could find the true luminosity of any variable star, she would know the luminosity of every variable star. We know based on the brightness equation that if we have the distance to a star, we can find the luminosity. Our only tool for measuring large distances in space at the time was parallax, and that could only measure 100 light years out. So if variable stars could be found within 100 light years of Earth, she could measure the distance from the star to Earth using parallax, and use that distance with the brightness observed on Earth to calculate the star's luminosity, and use that luminosity to complete her graph of all variable stars. So after she published her paper, astronomers did make observations of variable stars within 100 light years of Earth, and used parallax to measure their exact distance, and then calculated their luminosity using the distance and the brightness observed on Earth, and recorded the period of the star, which allowed them to place that star on her graph. They did the same thing with several variable stars, where they would calculate the luminosity based on the brightness and the distance they could observe, and the period of the star, and place that on her graph, and do that one more time. So again, they calculated the luminosity using the brightness and distance, found the period, and placed that on her graph. And once they had that absolute data filled in, and they had her graph with the predicted proportions of the period and the luminosity of any star, they were able to fill in the entire graph with this information. A variable star with a period of 1 day had a luminosity of about 300 times the luminosity of the sun. A variable star with a period of 10 days had a luminosity of about 3,000 times the luminosity of the sun, and a period of 100 days had a luminosity of about 30,000 times the luminosity of the sun. And just for reference, the luminosity of the sun is 3.85 times 10 to the 26th watts. So now that they had this information, they could use this to find the distance to any variable star that they could observe. And the farthest variable star that we can observe is about 20 million light years away. So as an example, they could look at a variable star in the far, far distance, way beyond anything that parallax could observe, and they could make an observation like this. They could observe, oh, this star seems to have a period of 100 days, and its brightness observed on Earth is 4.57 times 10 to the negative 17th watts per meter squared. So how far away is this star? We don't need to use parallax, because we can now use the period and Leavitt's graph of luminosity to find what the luminosity of the star is and plug that into the brightness equation. So if the period is 100 days, I can see that the luminosity is 30,000 times the luminosity of the sun, which is equal to 1.16 times 10 to the 31st watts. Using the brightness equation, if I have the brightness and the luminosity, I can rearrange the equation to find the distance to the star. Plugging in my numbers gets me a distance of 1.42 times 10 to the 23rd meters. Converting that to light years gets me 1.5 times 10 to the 7th, or 15 million light years. So I just measured the distance to a very, very distant star, only using its period and its brightness observed on Earth, and the observations made by Leavitt of the pattern between the period and the luminosity. So this ability to measure the exact distance to any variable star allowed astronomers to make a much more detailed map of the universe, because variable stars are clustered in galaxies, because all stars are clustered in galaxies, and scientists were able to understand the shape of the Milky Way, the shape of other galaxies, and the really vast distances between galaxies that we'll talk about in another lecture video. but the pattern of Cepheid variables that Leavitt observed is what allowed us to be able to do that. One very last note, variable stars are in a group of space objects called standard candles, which are sources of light that follow some standard rule that allows us to calculate their luminosity and therefore their distance, using the brightness equation. Standard candles are used to determine the distance to individual objects in space that we can observe from Earth. So if you're using a standard candle, you're also going to be using the brightness equation and the understood luminosity of the object. That's everything that you need to understand about the nature and history of Cepheid variables and how to use their properties to calculate their distance even at incredibly large distances.